You're about to learn how to create your own 2D game development engine in Java from scratch. Gabe from Games with Gabe created this comprehensive Java course over many months, and we're excited to put it all together into this massive course.
Hey guys, what's up? My name is Gabe, and this is Games with Gabe. This is the first episode in a new series, Coding a 2D Game Engine in Java. So I'm really excited about this series because we will be learning a lot of things about how games work in general and how to code a whole engine yourself. So this will hopefully be a great series. What we will be building was featured in the intro of this video. So what you saw is the final game that we will be building with this engine. It's not the only game you can build with this engine. It's just a game that I decided to make because it is a significant icon that has been really famous, and I figured what better game to highlight what we can do with this engine than Mario. So I hope you guys stay tuned. This episode there will be no coding. This will be purely explaining what features we will implement in this engine and what techniques and skills you will learn from this series. So I feel like that's a little bit cheaty, so I'm also going to release the actual first tutorial, which will highlight starting the window and setting up the project and all that good stuff. Okay guys, I hope you enjoy this though, and stay tuned to see what you will be learning in this series. Alright guys, so what will we be learning in this whole series? We're actually going to be learning quite a bit. The first thing that we will be learning about is LWJGL. So that's the lightweight Java game library. I say we'll be learning about it, but really we're just going to be using it as the framework for our game engine. And so what this is you may think this sounds like, oh, we're going to be using a game engine since this is a game library, but that's not true. What this is it's basically a wrapper around some graphics libraries and stuff that we will need when we are coding our game engine. And so this basically gives us the bindings to the C code so that we can use it in Java. So it's really helpful because it gives us the speed and the flexibility of all the graphics libraries that are written in C, but we can use it in Java. Now, what libraries are we going to be using? We're going to be using OpenGL and GLFW for the window handling and for the graphics. So OpenGL stands for Open Graphics Library, and it's basically an open source graphics library. And a graphics library just means it gives us access to uploading data to the GPU and allows us to draw things using the GPU and all that stuff. And it gives us functions that allow us to communicate with it and send data back and forth and all that good stuff. Then what GLFW stands for is Graphics Library Framework, and so all that is it's our window handler. It basically gives us a way to create a window and handle that window, listen for key events and everything, regardless of the operating system, so we don't have to worry about specifics of window handling, which is really nice when you're starting off and learning how to do this stuff. So one of the things that we'll be learning how to do that's different from sort of what we were doing before is rendering. Now, when we use these graphics libraries, we can't simply just say draw a square. We actually have to create something called a mesh, send it to the GPU, and then use a shader to describe how to draw this mesh. And then we're going to implement this final feature called bashing, which will speed up our rendering quite a bit. So typically with batching, this basically speeds up your rendering times because instead of drawing every single square, you can draw them all in one big batch, which is exactly as it sounds like. Now, these are just some pictures of some spheres being rendered with PBR, which is something that we could eventually get to. And I definitely do want to get to that once we start the 3D version of this engine. Now, next thing we're going to be learning about is animation systems. And so the system that I decided to teach you guys is the finite state automata. Now, basically what a finite state automata is exactly as this picture shows. It's basically just a few different states with transitions between each of the states. And we will use this to create our animation systems, and we'll have animation states and then animation transitions that we'll be able to trigger. And this will be really nice when we go to create all those different animations we need to attach to our game objects. And we're only going to be doing sprite-based animation, but we will be implementing keyframes so that you can time out your animation in different lengths and stuff between each of the time steps, which is nice. Another thing we're going to be learning about, physics. Every good game needs physics, and so we're going to be doing our physics sort of a tile-based physics for the static objects, and then for dynamic objects, we'll implement a little bit of a different system. We're not going to be doing anything too smart with the physics just yet, but it will be basic box collision detection and collision resolution so that we can have our characters moving around the screen, detect which side they're hitting and everything, and then pass that on to every single component so that if they need to respond to a collision, they have the ability to do so. One of the last things that we're going to be learning about is user interfaces. So this is a picture from the actual game engine, the final features that we'll be making, and you can see we have these windows and these buttons. We are coding all this by hand. We will be coding how to draw every single little bit of this window, to the interactability of when the mouse clicks on buttons, what to do, when to do it, all that good stuff, which is really important to know how to do in case you are ever in a situation when you need to code it yourself or when you need to understand why something is misbehaving. So this will give you a little bit of a deeper understanding of how user interfaces work in general. And then one of the final things I feel like gets skipped over too much and really shouldn't be, because this is one of the most important steps in building a game, is packaging and distribution. So I will be showing you how to package your Java game into a jar file so that you can distribute it through different websites and allow your friends to play it on whatever machine they are operating on. And you'll know there's actually a link in the description that you can click on to download the final engine and the little game that I made with it, which is sort of what we'll be doing too when I show you how to package it and distribute it, because these are really important. If you want to share your work with the world, you need to do this. And then finally, what we're going to be doing is putting it all together using the game Mario. So this game you may think is actually really simple, and in a way it is if you're using something like Unity, which has all the features built in already, but it has a lot of complex features that are actually test all your skills. Physics, it has sprite-based animation, it has complex game logic that you need to communicate with each other. You need game objects to be able to find each other and communicate with each other smartly. It also has a pretty complex level editor. If you want to build the levels pretty easily, you need to put a little bit of work into how you decide to design it so that the user can actually drag and drop different things and all that good stuff, connect pipes, doing all of that. And it's actually pretty hard to get optimized correctly. So when I first started coding, I thought this would be a good game to start coding. It's simple enough. And I actually couldn't even start my browser. So I coded it in JavaScript and it just crashed my whole browser because of how slow it was. So it does require a little bit of forethought. You can't just slap something on there, slap some sprites together and throw in all the objects and hope that it all works. You have to put some thought and you have to put some consideration into how you design it. So this will be a final test of our engine, and it's what we will use to basically just make sure that our engine is working well. In this episode, what we're going to be doing is coding or setting up our project and getting a window started. So we will set up our LWJGL project in IntelliJ, and then we will get a window up and running just so that we have the basis to start working. If you haven't checked out the last tutorial, you should definitely check that out because that goes over everything that we will be covering in these tutorials. So let's get started and start our project and set up the window. Alright guys, so if you haven't already, open up IntelliJ and then hit New Project. Now I have the project window open up over here. What you're going to want to do is go to the left hand corner and select Gradle. We're going to be using Gradle for our project because this will allow us to import all the libraries for LWJGL into our game. So then you'll just hit Next, and then Group ID is just if you're doing a Maven repository, which we are not. And so that just helps that out. We're just going to worry about the artifact ID, which is basically what our project's called. I'm just going to say Mario because that's the end goal of this. Next, select where you want this to go. So I'm going to go into C, Dev, and then I'm going to hit a new folder. And I'm just going to call this Mario for YouTube. And then I'm going to hit OK and Finish. Then it's going to ask you to open up the project in a new window if you have a window already open, and you can just hit this window. Next thing you're going to want to do is go to LWJGL.com. Now will include the link in the description, so you'll get to a link that looks like this, and then we're going to say customize LWJGL. So it'll take you to this, and you're going to click onto minimal OpenGL first. So this will get us all the minimal OpenGL libraries, and then you can hit show descriptions, which will show the descriptions of each library. Make sure you check JOML. JOML is the Java math library that we will be using for our game. And then just make sure you have 3.2.3 selected. Then it will have async selected already. This is for importing 3D models. We won't be using this library, but it's good to have once we do switch to 3D. GLFW, which is the window handler that we will be using in this tutorial specifically. Make sure you check native file dialog. We will be using this to open up file dialogs for any operating system. OpenGL is the audio library we will be using. OpenGL is the graphics library we'll be using. And STB is so that we can load images, fonts, all that different stuff, sound files and everything. And that should be it. And then you'll notice also too, make sure you have Gradle selected, because then you'll get at the bottom of the screen this text. And what we're going to do is we're going to copy all of this and we're going to open up our IntelliJ project and double click onto the build.gradle. So once you open up the build.gradle, it should look something like this with very minimal things inside. Paste that code that we had right up there into the file, and then just take out this repository as Maven Central because we already have that up here. Now all this is sort of like a build file for Java. It just allows Java to know, hey, we're going to be using all these libraries, and then it can import them online for us. And then it also specifies the version of our project, which we're just saying is 1.0, and the compatibility. So we want to change this to 1.11 because we will be using Java 1.11 or above, and you can switch this to whatever you want. 1.11 is the minimum that we will be supporting. And then next you'll just notice that all these different things are just basically importing all the libraries that we had. And it's going to pop up a little thing over here. Gradle projects need to be imported. Hit import changes. And it should say configure successful, which means it's now imported everything inside of our Gradle, inside of our project. Next thing we're going to do, we're going to want to go into main Java and we'll create a new class, and this will be our main class. So this will be the entrance to our program, and we're just going to create a main function. So just the standard main function. And then what we're going to do inside here is basically we're going to create a window, which we do not have right now, by calling it. So this window is going to be a singleton, which if you've watched some of my previous tutorials, the Geometry Dash in Java and Snake tutorials, we went over that in a little bit more depth, but it basically means we get it via the class definition. And then we're just going to say window.run. And so these are all functions we're going to be creating right now. Next, we're going to go in here and we're going to create a new package. So I'm going to call this Jade because that's the name of the engine that I've given it. Then we're going to go into Jade and we're going to add in a new class, and we're going to call this window. So this is the window class that we're going to be making. Now we need window.get and we need window.run. So let's go back into here real quick. First, let's create a private constructor. Reason we're making this private is because we don't want any outside things to create a window. We only ever want one window class, and this will ensure that it is a singleton and only the window class can create it. We're going to need a few variables for our window. We're going to need the width and the height, and we are going to need the title. So we'll have all those up there. And then we'll just initialize those inside here. We'll say this.width equals 1920 or whatever you want. This.height equals 1080. So I'm just giving it a standard HD definition. And then we'll say this.title equals Mario. And then we're going to go up here to make these private because we will be trying to do private variables and everything for this tutorial because it is helpful so that we can control what happens every time these are changed. Now we'll create that get function. So the get function will be a public static window is what it's going to return, and we'll just call that get. Then what we can say is up here we will create a private static window object, and this will be our singleton. So we'll ever only have one instance of the window, and we'll initialize this to null up here, and we'll basically just say inside here if window.window is null, then window.window equals a new window, and then we'll just return window.window. And so all this means is the only time the window is ever going to be created is the first time we call window.get right here. And from then on, it will be calling just this single window object so that we don't have a bunch of different window objects because inside of our game engine, we are only ever going to have one window. That's the reason we're doing it this way. So the singleton, there you can read up more on that and stuff too to get a little bit more in-depth information about it. Next, what we're going to do is we're going to create the run function. So this function is going to do a few different things. So we'll say public void run, and we're going to do a lot of the stuff that is inside. If you go to the LWJGL website and you hit get started, it gives you this nice hello world class, which basically puts up a window. So a lot of the stuff that we're going to be doing in here is literally just copied and pasted from here to set up the window, because that type of stuff you only ever really do once. Now inside here, what we're going to do is we're going to say system.out.println hello LWJGL plus version.getVersion. This is just helpful so that you know that LWJGL is working. This is also taken directly from that tutorial. And then we're going to call a couple different functions. We're going to say init and loop, which we have not created yet. So let's create init first, and then we'll fill in loop after we create the init function. So we'll say public void loop down here. So for our initialization function, we have to do quite a bit to get our window up and running. With the previous series, we really just had to do a couple things and then the window was up, but here we have to do a lot of things manually. So first thing we're going to do is set up an error callback. And the error callback is basically just where the GLFW will print to if there's any errors. And we want it to print to down here in our build log, which is where we'll be looking for most of our info and logging information, everything. So we'll say GLFW error callback dot create print, and then we're going to say system.error dot set. And so what this is going to do is it's just going to create the printing method for where the errors will be printed to, and we just say system.error. So it would be the same as you saying system.error, we have an error, or something like that. System.error.println, something like this. And that's basically all that this will do, is it's just going to direct all the errors to do something like that. Next, we're going to initialize GLFW so that it can set up our windows. So we'll say if not GLFW init, and hit Alt Enter to import that. Say throw new illegal state exception, unable to initialize GLFW. And once again, this is all taken directly from that little intro tutorial. We're basically just saying this function will return true if it succeeds in initialization and false if it does not. And we'll just throw an error if it does not succeed. Next, we want to configure GLFW. So we're going to say GLFW default window hints, which gives it all the default window hints. Window hints are basically just like, do you want it to be resizable? Do you want to have a default close operation? Do you want it to be visible? Things like that. And so we're going to set a few of these window hints now. Say GLFW window hint, and then we're going to say GLFW visible is GLFW false. And the reason we're doing this is because we are going to have it as not visible until we are done creating the window, and then once we're done creating the window, we will make it visible. And then just import static. Make sure you import the static methods right here. If you hit Alt Enter, it'll bring up this little window, and then we can import all of those. Then we can say GLFW window hint, and we'll say GLFW resizable is GLFW true, which it should be by default, but we're just putting it there. And then last one, GLFW window hint, GLFW maximized is GLFW true. So this will make sure that when the window starts, it is in the maximized position, which is nice because a lot of times that's what you want. Next, we're going to actually create the window. So we're finally getting around to creating the window. And the reason we set these hints before we create the window is because GLFW will now use these hints to create the window. That's why we want it to be false as visible, because we want to wait till it's finished creating it. So say GLFW window, which is a variable we're going to create, equals GLFW create window. And we're going to say this.width, this.height, this.title, and then we're going to say null, null, all caps. And then you can import this. Just make sure you import it from memory util, so memory util.null. And now, what does GLFW create? It returns a long. So it creates a long, which is just a number. So say private long GLFW window, and we're just going to set that to nothing at first. And so basically, what is this number? This number is a memory address where this window is in the memory space. So GLFW is returning us this long, which is a number where the window is in our memory space, so that we can handle it. Because that's the way you do things in C, and we're kind of doing that with our code right now. And then we just pass it in the width, the height, the title, And you'll notice the last two parameters are the monitor and whether we want to share it, which we're just saying to null to let it know, hey, we don't care about the monitor or sharing. And then that will just create it on the primary monitor and not worry about sharing. Then we'll say if GLFW window equals null, that means that it did not create the window. We'll say throw new illegal state exception failed to create the GLFW window. So that's also directly from their tutorial. Next, what we're going to do is we're going to make OpenGL the context. So we're going to make the OpenGL context current. I'm sorry. So we'll make the OpenGL context current. And this is as simple as doing make context current GLFW window. Then we'll enable vsync. And this is basically just buffer swapping. So we'll say GLFW swap interval is 1. And so vsync just means there's no restriction. This is basically saying just swap it every single frame. There's no wait time between the frames, between how long we wait. And so this way we'll go according to the refresh rate of the monitor. Or not according to the monitor, but we'll go as fast as we can, which just means we're enabling vsync. So that's all that means. Next, the window is now created, so we'll make the window visible. So we'll say GLFW show window, GLFW window, which is our pointer, our long number to our window, which we created up here. So this is finally, we have our window created. And then the last thing we have to do is we have to say create capabilities, gl.create capabilities. And I'm going to copy this long comment in. This was also on their website. So it says this line is critical for LWJGL's interoperation with GLFW's OpenGL context or any context. So this basically just makes sure that we can use the bindings. This is really important. You cannot forget this. It will break if you do not have that in there. So this is the initialization. We have the window initialized. Now we have to loop through and actually start our loop. So we'll say while not GLFW window should close, and then we're going to pass it the GLFW window. So the pointer to our window, that number, we'll say first we're going to pull events, which is just getting key events, mouse events, all that stuff. We'll say GLFW pull events. That will pull it and get the events into our key listeners, which we'll set up in the next tutorial. We'll say GL clear color, and I'm going to set it to red just so that we know for sure that this is working. So this is RGBA, one is from 0 to 1. So we just say full red and then full alpha, which gives us a red color. And then hit import static method, alt enter to get that pulled up. Make sure you choose GL11 without the C, and that should be good. Then we'll say GL clear, GL color buffer bit. This tells OpenGL, the graphics library, how to clear the buffer. And so this is basically saying use the color buffer bit, which takes in what we just put in here. We set the clear color here, and then we just say, okay, now flush that clear color to our entire screen. And that's what that does. And then lastly, we have to say GLFW swap buffers, GLFW window. And so this will swap our buffers automatically. We don't have to worry about that. OpenGL handles all that. OpenGL and GLFW handles all that internally and just swaps the buffers for us. So this should be everything. And now if you hit first run and hit edit configurations, nope, hit build. And so we should get a successful build. And then if we go into main, this should be working perfectly. Then we'll hit run and hit main. And you should get a red screen. So the window is maximized. And if you minimize it, it'll go to 1920 by 1080. And you can resize it, which is what we said. And the title is Mario. So this is a lot of work, as you can see, just to set up a simple window. If you follow my last tutorials, it's really easy to set up a window. And here, there's quite a bit you have to do. And the reason for that is because we're just going at a much lower level, which will give us a much better advantage in terms of speed and everything. So that's the whole reason it's harder, because we're getting closer to the hardware. But we'll also learn a lot more. So just a quick review, what we did was we initialized the window through all these different functions. We have to initialize GLFW, which handles creating the window. We set the window hints. Then we actually create the window. We check and see if it succeeded. Next, we make the window current. So we check and we make the window our current context. We enable vsync. We make the window visible. And then we call this gl.create capabilities, which gives us our bindings to OpenGL, the C bindings. And then lastly, after the initialization is finished, we enter our loop, which basically says while the window should not close. We should pull the events, clear the screen, and then swap buffers. And then if we change this clear color to white, which is what I'm probably going to have it at for most of the time, we'll get a white screen. So this is creating the window. The next tutorial, what we're going to be doing is creating our key listeners and our mouse listeners and all those different things. So we'll be setting up the bindings, which will happen sort of in this initialization function. And we'll be setting up a rough, basically just getting key events and stuff. And then we'll make sure it works by calling it inside of this loop. So in this episode, what we're going to be doing is setting up key listeners and mouse listeners. And these events are actually pretty easy, so I'm not going to belabor the topic. We're just going to sort of move through it. It is different than when we did it in the auth library because we have to do things a little bit more explicitly, but it's still not too bad. And I'm going to show you a cool trick we can do at the end to fade the screen to black after we set them up on a key press, just so that we can explore what we've done. I'm also going to show you how you could set this up with gamepad controllers and stuff if you really want to, because GLFW gives us that opportunity. Okay guys, so let's see how to do that real quick and let's get it done. So before we start coding, I did want to go over something simple because I think in the last series I did this a little bit weird, and that is the dx and dy values. So when you are in your game engine and you have the mouse move, you have these values called dx and dy, which basically represent, so say that was the position on frame 0, and then the mouse moved to this position on frame 1. So it's moved this distance vertically and it's moved this distance horizontally. And I think what I was doing was I was saying like the absolute position. So say this was 0, 0. I would say, okay, the mouse X, mouse Y is now, this is 2, 1. And I would say, and dx dy is 0, 0, which makes no sense. What it really should be is dx dy is this value right here, which is 1. It's traveled to hold a distance of 1 in the dy direction, so delta y, and then delta x is equal to 2 because it's traveled 2 units to the right. And so this is really what I just want to make sure we fully understand is when we're coding these dx dy values, we do want to set these to the distance elapsed between the last frame. And in order to make sure that this is always correct, we also need to reset these at the end of every frame. So we need to call something called end mouse frame, which will end up resetting these values to 0, because if we're using these dx dy values and the mouse has not moved at all, then it has moved 0 units in the right and 0 units up and down, which is exactly as it should be. And we just want to make sure we're resetting that, because if we don't, then we can get some weird bugs. So dx dy position, we travel in the vertical and horizontal direction, and we reset those at the end of the frame. Now let's code this. Okay, so we will code those in just one moment, but before we do, I want to go over one last thing I forgot to do. So we create this whole window and everything, and when we're doing this in LWJGL, it actually does it a little bit differently. Since we're using C bindings, we allocate resources, memory. We're allocating that ourselves, and Java is not handling that memory. And so when we create a window and everything, we grab a chunk of memory, and if we want to be proper, then we should free the memory once our loop has exited. So right here inside this run function, what we should be doing is we should say GLFW free callbacks, and this will free any callbacks that are attached to the window, which we don't have right now, but we will in just a second. And then GLFW destroy window, and we pass it the GLFW window. And then we want to terminate GLFW, and we want to free the error callback. So these are the last sort of error freeing, resource freeing methods that we have to call. So free the error callback. So then we would say GLFW terminate, and then GLFW set error callback. And we would say null because we're setting the error callback to null, and then we free it, we free the memory. And so this isn't strictly necessary. The operating system will clean all this up for us if we don't do it, but if you want to be proper, you should add it in. And this was also included in that tutorial that was linked to the LWJGL.org site. So add those in if you want to be proper, and it's all good. Next, what we're going to do is we're going to create our key listener and our mouse listener. So we'll create a class, and we will call this mouse listener. Since this one's a little bit more complicated, we'll do this one first. And we want to set up a few things. So this is going to be a static class. So what we want to do is we want to give it a static instance. So we'll say mouse listener instance. And this is going to be our singleton. So this is the singleton of the mouse. And we're going to create a few variables that we will keep track of. Scroll X, scroll Y, and then we also want some doubles, X pose, Y pose, last Y, and last X. And those will be for our DX, DY values and stuff. And then what we'll do is we will have a Boolean array, mouse button pressed, which will store which button was last pressed. We'll say is a new Boolean, and we'll initialize it to 3. I believe there could be more, but 3 is the only buttons on this mouse, so I don't have to worry about it, and you typically don't have to worry about people pressing more than that. We'll add a catch in there just in case there's more than 3 buttons. And then we'll add in another Boolean is dragging, which will let us know whether the mouse is dragging or not. And that should be good. We'll have to add in a few more variables once we start doing projections and stuff, but for now we are good. Projections, which means we're just matching the screen to fit how many pixels we would like it to look like are on the screen. So we'll get to that a little bit later. But let's create a private constructor now. And reason we're doing this private once again is because this is a singleton and we don't want this to be public to other classes. The only class creating this should be the mouse listener class. So we'll say scroll X is initialized to 0, scroll Y is also initialized to 0, X pose is 0, Y pose is 0, and last X is 0, and last Y is 0. It is important that you initialize these values because if you're using them and the very first frame, you can get some weird bugs if you don't have these initialized to 0, because it will be like, oh, the mouse is in some random memory position or something like that. So just make sure you do that. Then what we're going to do is we're going to create that get function, which is very simple. We did this in the last tutorial too. So we'll say public static mouse listener, and this is going to be called get. And we're going to say if instance equals null, which it will on the first time we call this, then we'll say instance equals a new mouse listener. And then we'll just return the instance. And if you want to be more specific, you could say if mouse listener dot instance, just so that you know exactly what you're talking about. And then you could just say return the mouse listener dot instance. Okay. Next, we're going to actually create the callbacks that we will be calling. So in order to figure out what callbacks you would have to do, you could go to GLFW callbacks, the input guide. Then it has all these different titles and everything. It shows the GLFW pull events, wait events, all the different things they give us. Then it says keyboard input, and we see this thing called key input. And it says we need to set a callback, a key callback. And then for the key callback, we need a function that looks something like this. This isn't C, so it's going to look a little bit differently than when we use it with LWJGL. But typically, you just replace this with a long instead of this GLFW pointer, which is what that star is. Then you'll be fine, and then everything else will remain the same. The one we're looking for is mouse input, so we want this static void cursor position callback, which is the first one we'll implement. So let's go back to our code real quick, and we'll say public static void mouse pose callback, which will take in a long window. And then if we remember, it had an X position and a Y position, both doubles. So then we'll say double X pose and double Y pose. And it's important that these match that callback because we will need this exact definition in order for it to work properly. Then we'll just say get.last X equals get.X pose. So we're setting the last X and the last Y before we change it to the new X and the new Y. So basically we're saying get to get our mouse listener, and then we're just grabbing the variable and resetting it according to what it needs to be. And then we're going to change what the variable actually is now. So then we'll say get.xpose equals xpose, and we'll say get.ypose equals ypose. And then we'll see how that goes once we get to it. Now we want a mouse button callback. So let's go back to here, and we will look for a mouse button callback. So it has cursor mode, raw mouse position, cursor objects. We keep going down. Cursor, enter, leave, mouse button input. Here we go. So then we see it says there's a mouse button callback, and then the definition looks something like this. We have the window, the button, the action, and the mods, which are just modifiers. So we'll go down to here, and we'll say public static void mouse button callback. So mouse button was pressed, takes in a window, and then let's go back to there. and it takes in a button, an action, and modifiers. So we'll say int button, int action, int mods. And modifiers are just like if you were pressing the control key while you clicked or something like that. So that's all that modifiers are, which you need sometimes if you're checking for like control C or something like that. You have a modifier key being pressed while you press another key. So then we'll say get dot mouse button pressed. And then we'll say button equals true. So the button was just pressed. Actually, was the button just pressed? We don't know. You do have to check one more thing. So we can check if it was pressed or released. If we say action, so if action equals GLFW press, then we know it was pressed. And we can import that hitting Alt Enter. Else, if action equals GLFW release, then we know it was released. We can say get that mouse button pressed button equals false. And we will turn that off. And if it was released, we also know that if it was dragging, it is no longer dragging. So we'll just set that real quick because we know it's no longer dragging. Now, what if the mouse has more buttons than we have programmed into our Boolean? We only set 3. We should check for that because just in case you have one of those fancy gaming mouses, I don't know, and you press more than one button, you don't want that to throw an error here. So we'll say if button is less than mouse buttons, get dot mouse button pressed dot length. We'll set it. Otherwise, we'll just ignore it. And then we'll do the same thing here. Well, actually, we'll just copy that and check and see if we have enough room in that array to store that. That way we can just catch that just in case. Next, we want the mouse scroll callback. So we'll keep scrolling down. Hey, scroll input, look at that. So we have a scroll callback, takes in a window, an X offset, and a Y offset. So we'll go back into here and we'll say public static void mouse scroll callback. And we'll take in a window and we'll take in, I believe it was a double X offset and a double Y offset. And we can just say get dot scroll X equals X offset and get dot scroll Y equals Y offset. And I spelled scroll wrong. And you may be wondering, why am I doing the get? Well, that's because we're making all these static. Because when I'm coding inside my application, I don't want to have to do mouse listener dot get dot. I want to be able to just say mouse listener dot is mouse pressed and pass in a button, GLFW button 1. And that's how I want it to be. So if we make all these static, then we can call all these functions statically, which just makes it a little bit easier. And also, the callbacks do need to be static because when we're passing them to our callback handler, it's easier if they're static than if they were member variables and stuff. So we'll see that in just a second too. Now, that is it for the callbacks that we need. Let's add the end frame function that I was talking about. So we want to make sure that we're ending these frames. We'll just say get.scrollX equals 0. We'll reset the scroll and the deltas. So then we'll say get.lastX equals get.xpose, which will inherently set the deltas to be 0 because now if the last X and the last Y are the X and Y that we're currently at, when we subtract those two, we'll get 0. So that's what we do. Next, we'll make all our static getter functions. We'll say float get X, which will be like get where the mouse X is. We'll say return float get dot pose X or xpose. And then I'm just going to copy this whole thing. We'll do get Y. And so instead of X's, we'll just say Y and we'll say Y. Next, we want get dx. So I'm just going to copy this again and we'll say get dx. And this one's going to return the X, the last X minus xpose. So we'll say get last X, and I'm going to wrap this in parentheses so that we cast this whole expression to a float. And then we'll say minus get.xpose. And that will just give us the amount of elapsed X position in the current frame. Then we'll say get dy, if I can type right, and change this to Y, change this to Y. And then next we want scroll X and scroll Y. So let's say public static float get scroll X. And there is scroll X, some mice, I'm not sure what the plural of that is. They do have a scrolling in the X and the Y direction. So that might be useful if you want to do that. So we'll just say get.scroll X. And then we also want scroll Y. So we'll do this one more time, and we will change this to a Y and change this to a Y. And we want if it's dragging. So we'll say public static boolean is dragging, return get dot is dragging. And then next we want, I think that's it. Mouse button down. So we want to check and see if a mouse button is down. So we'll say a static boolean mouse button down, and we will take in an integer for the button, which is what GLFW gives us. So GLFW mouse button 1, we have all these different things, and those are just integers. So we'll say return get dot mouse button pressed, and then we'll say button. And we'll do that check inside here too, just in case. We'll say if button is less than get dot mouse button pressed dot length. We'll return this guy. Otherwise, we will just return false, so that we have our bases covered and we will not get any errors. Now, is dragging, how do we know if it's dragging or not? Well, the way that GLFW calls our callbacks is it calls the button callback and then it calls the mouse position callback every time the mouse is moved. And the way we've set it up is if we get our mouse button callback called, so if we look up here, we have our mouse button callback, we say if it's pressed, we set the button to true. So while it's pressed, we won't set this to false until it's released. So while it's pressed, we know that one of these will be true. How can we tell if the mouse is dragging? Well, if the mouse position moves and one of those buttons is pressed, then we know it's dragging. So we can say is dragging equals, and we'll say get dot mouse button pressed 0 or get dot mouse button pressed 1 or get dot mouse button pressed 2. That's kind of long, but it's really simple. So basically what we're saying is if any of the mouse buttons are pressed and the mouse has just moved, then clearly the user is dragging something now. So we just do this or statement, which basically says if this is true or this is true or this is true, then this will all be true. So that's how we check for dragging, and that should be it for our mouse listener. How do we register these callbacks now? Well, in Java 8 and above, I believe, it might be 11 and above, we have these things called lambda expressions, which is basically what GLFW is going to be expecting. So inside of our init loop, this is where we would set up our callbacks, and we would do this right after we create the window, because we need a window in order to set a callback for that window. So we'll do it right down here, and we can just say GLFW set cursor pose callback, and we'll say GLFW window, which is the window we want to set this callback for, and the function we want is mouse listener, do a colon, and then you notice we get all of our functions, and we want mouse pose callback. So this colon is something you may have never seen before. It's a Java syntax that's basically shorthand for lambda function. Lambda functions are just stuff like x goes to some function x, and we want to return, it's something like this, x plus 2 or something like that. And basically it just plugs in x everywhere. I think it might just be something like this. But basically you have these things called lambdas in Java where it just sort of forwards things to a function. We're saying forward your position callback to this function. And that's what we want it to do. We want it to call our function whenever there's a cursor callback. Next we'll say GLFW set mouse button callback, GLFW window, mouse listener, and then we'll say mouse button callback, GLFW set, and we want our scroll callback. We'll say GLFW window and mouse listener, and we'll say scroll callback, mouse scroll callback. And that should set up all of our mouse listener callbacks. And how do you know to call those functions? Remember, they showed us them right here. So these are where you would get where to call those functions, and then these are where you would get the function definitions at the GLFW.org docs so that you know exactly what to call. Next, let's do our key listener. So we'll make a new class. This is going to be called key listener. And this one's actually going to be a lot easier because key listeners are just a lot less to deal with, really. There's not a lot of events that could happen for a key listener. So we'll say private static key listener instance. We're making this a singleton, just like the last one. And we'll say private boolean key pressed equals new boolean 350. I'm not quite sure why I chose that number. I'm looking at my old code. I think it may be because I Googled what the amount of key bindings that GLFW has, and it might be 350. Okay, and then we'll make a private constructor just to make sure that no other classes call this. It's going to be empty because we don't really need to do anything. When you create an array in Java, it initializes that array to be empty, full of zeros, which is what we want. So, or false, which is what we want. Then we'll make a key callback. And this takes in a window and a key, and I believe it takes in an action. Nope, it takes in a scan code, action, and modifier. So we have a scan code, we have an action, and we have mods. So once again, the modifiers are just any keys that are pressed in addition to this key. The action is like GLFW key press, key release. Scan code, I'm not completely sure on. I'll have to check the docs on that. And then key is just which key was pressed. We'll say if action equals GLFW press, then we will say get.key pressed. And we'll say key equals true. Let's create that get function real quick too, just so that we have that. So we'll say public static key listener get, and then we will say that if the key listener dot instance equals null, then the key listener dot instance equals a new key listener. That will initialize our key listener first, and then we'll just say return key listener dot instance, and that should take care of the get function for us. Then we'll say else if action equals GLFW release, then we want to set that to false, so we'll just say get dot key pressed key equals false. Whoops. And then we can import that, alt enter. And I'm not going to check and see if these are inbounds because I believe I captured all the possible cases with that 350. If I'm wrong on that, comment below and I will add an addendum to this video just to let everyone know. Then we'll make our getter function. We'll say static boolean is key pressed, and we'll pass in the key code we want to check for, and then we'll just return get dot key pressed and key code. And if you want to be really safe, like we were in the last one, you could wrap this in an if statement. We could just say if key code is less than get.keyPress.length, we'll return this. Otherwise, we'll return false. Just in case if the user passes in some junk, we want to make sure that they don't get it. You could have it return the error though. I don't know. I think I might want this to return an error because if the user passes in some junk, they may not know that they're passing in some junk. That might be an error with the program, and I think I'd rather that throw a null pointer exception or an array out of bounds exception so that we know, hey, something is going seriously wrong because we're getting a key press that should never exist. But that should be it. Now let's register this with our window. So we'll go to here and then we'll say GLFW set key callback, give it the window, and we'll say key listener, and we'll say key callback, which sets up all our listeners. So now all of our listeners are set, and we should be able to query for key events. So let's go to our loop. We have our pull events right here. Then we have our clear color. Let's just test this out real quick. Say system.out.println. Well, actually, we'll just say if key listener dot is key pressed, and then we'll say GLFW key space. Then we'll say system.out.println, and we'll say space key is pressed. So if we run this real quick, and I'm going to make the window smaller, and if you hit space, you notice it says space key is pressed. So that's good. That's telling us exactly what we need to know. I would go through and test all the other functions we did just to make sure they're all working properly if I were you. I believe they're all correct. If they're not, we'll have bugs later on and we'll find out about that. But that looks good to me. Now let's do a cool thing real quick. Instead of doing this, let's go up here real quick. We'll just say private float RGBA, and we'll go down to our creation function R equals 0, B equals 0, G equals 0, and A equals 0. And let's create a cool little fade to black thingy when you press space. So right now we will pass in R, G, this is going to be B, and this one's going to be A. And let's actually set those to 1 because that's probably better. 1, 1, and 1. And then what we can do is we can say if the space key is pressed, we'll fade to black equals true. And then let's just go up here real quick one more time and we'll say private. This is not going to stay 2, so if you don't want to copy this, don't copy it. Fade to black equals false. And then we can say, since this is now true, we'll just say if fade to black, then r equals math.max, r minus dt. Oh, do we have dt? We don't have dt. We'll add that in the next tutorial too. Say r minus equals 0.01 f or 0. G equals math.max, g minus 0.01 f or 0. And then b equals math.max, b minus 0.01 f or 0. So now we should get it to fade to black when we press the space key. So let's go into here, space key, and it fades to black. So cool, we have a cool little transition thing, and you can change this to any color you want. What's happening here is we're basically just saying decrease R, G, and B in equal distance every frame until it fades to black. So just a fun little thing that we could do to illustrate how this all works, and it happens when we press the space key. So we have some user interaction. And last other thing I want to mention is you can check for controller keys. If we go back to GLFW's documentation, we have this joystick input. So you can set up key listeners for joysticks, which is for controllers, joysticks, everything, joystick button state, and all these different things. They have it built in, and they will detect all this stuff for you. You just have to set up the appropriate callbacks, and it will work as you would expect. And then they also have the gamepad input. So if you want to make your game compatible with a gamepad, I highly encourage you to try this out. Check it out and see if you can get this stuff working, and then hook up your controller to your PC and see if you can get it to work. But that is it for this tutorial. I hope you guys learned something, and I hope this helped you out with how key listeners and mouse listeners work. In the next tutorial, what we're going to do is we're probably going to set up the delta time variable and get all that working. And then we are also going to start setting up our scene management so that we can actually do our tests and stuff in scenes instead of just sort of throwing code into this. Last tutorial we got to was we set up some event listeners so that we can listen to key events and mouse events, and now we have that cool little fade to black thing. We're going to actually use that fade to black thing to do something useful now. I know I said we weren't going to really be using it, but this is also purely just if you want to at the end of the video. What we're going to be doing today is setting up some scene managers, and we are going to be setting up the delta time variable. So delta time variable is very important because we pass that to the game to let it know how much time has elapsed since the last frame, which you can then use to time different game objects and stuff. And if you need, like, sprite-based animations is a good example. If you need them to run every 0.2 seconds, you can use that delta time variable to track that and make sure that you have that running every 0.2 seconds. And then we're also going to be setting up the scene manager, which is going to be helpful because that will help us separate our game logic from our platform layer. The window is our interface between our game and the operating system. So that's sort of our interface between the platform. And then our scene is sort of like our game code specific stuff. So nothing operating system specific should live in the scene. That should all be game code specific stuff. So let's get that done real quick and see how it goes. So before we start coding the time, I do want to go over some things with just like units and how we're converting. So we use this function called nanotime, and what nanotime is a function given to us by Java that uses the system to get our time in nanoseconds. Now, there are 1 times 10 to the 9th nanoseconds in 1 second. So that means if we want to figure out how many seconds elapse in 1 nanosecond, we would just flip this. So then we know that there is 1 times 10 to the minus 9 seconds for every 1 nanosecond. So this is just flipping it. And the reason we're doing this is because it's easier to think in terms of seconds than it is to think in terms of nanoseconds, because we have these units of measure like frames per second, and we have these other units that we want. When we think in time in games, we're typically thinking on the order of seconds. We're not thinking of the order of nanoseconds or milliseconds or anything, because it's just easier if you are, say, doing your sprite-based animations. You want to think 0.2 seconds. You don't really think, I need around 200 milliseconds. So it's just a little bit easier that way. And I don't even know if that's the right conversion that I just did in my head there. But then once we get our 1 times 10 to the 9 seconds, we know that's how much is elapsing each time. So we just need to multiply this by 1 times 10 to the 9th to get our time in seconds. Then if you want to convert this to like frames per second, well, frames per second is literally just how many frames are there per second. So that means you want to do frames over second. And so when we get our delta time variable, we know our delta time variable dt is the amount of time that happened in one frame. So it's seconds per frame. And so if we want to get from here to frames per second, once again, you would just flip it. So you do 1 over dt equals frames per second. And so that's how you would do that conversion, which we will do also just so that we can see how fast our game is running once we get that delta time variable in there. So I hope this quick explanation was a little bit helpful, but let's go and actually see how it works in the code, because I feel like that's always a little bit easier for me to understand than it is seeing the math behind it. So let's do that real quick. Like I said before, we're going to need our time variable. So let's start off by creating a simple class that will get us that time variable. And we'll just put a new package here, and we're going to call this package util, which is where we'll put things like constants and other things of that nature. And then inside this package, we're going to create a new Java class, and we're going to call this time. Time is literally this super simple class that we use just for the delta time variable. You might question why it's even useful, and I'd say just because it's nice to wrap things up so that you know exactly what's happening there. Now, what we're going to need is we're going to need a public static, I'm going to call this a float, and this is going to be the time started. So this is going to be the time that the game actually started. We're going to call this system.nanotime. Now, static variables are initialized at the application startup. So all of these are initialized as soon as the application starts up. So we know this is going to be the time of the application start, which is nice, and then it's never going to change after that. So then we can use that in conjunction with our function called getTime to find out the time elapsed in seconds from the time start of the application. So then we'll say return, and we're going to cast this to a float. We're going to say system.nanotime, which is the time that we're at now, minus time started. And then we're going to say times 1e to the minus 9, just like I showed you to convert from nanoseconds to seconds. And all this is doing is it's saying return the time that we're at now, so nanotime now minus time started, which gives us the distance. So this is the time elapsed since the application started, and we convert that to nanoseconds. So really simple, just the time since our application started. Now let's actually use this inside of our loop. So how do we use this inside our loop? Well, we get a couple variables. We'll have our float last time, so the last time that the frame ran, and we're going to call this time.getTime using our little helper function. Actually, let's call this begin time, so the time that the frame began, and then we're going to call this one float end time. This is the time that the frame ended. And so actually we're going to initialize both of these out here, and then we're going to say GLFW pull events, clear color, all this stuff, and then right here at the end what we're going to do is we're going to say, okay, so dt is end time minus begin time, and we'll actually get end time here again. So we'll say end time equals time.getTime, and then after that we'll say begin time equals end time. And then next time we come through here, dt will be the next time elapsed. So what happens here is begin time is initialized here. It's the time at this point. We go through, we run our entire game loop. We get to here and we record the time that we're at right here. We subtract the end time from the begin time, which happened here, which gives us the time elapsed that it took to do all of this stuff. And that's our delta time. Then we say begin time equals end time. So now begin time is here. It loops back around, and then end time gets the time again, and once again it's the time that it took to get from here all the way back around to here. So dt always contains that looped time. And the reason we're doing it at the end here rather than at the beginning is because what if your application goes through here and then the operating system calls some other function? So then you get a lag spike in your game. If you called begin time up here, you would just be recording the time it took to cross over here, when in reality the operating system interrupted your game, and it actually took a couple of milliseconds out from here to here, and then those milliseconds added up inside of here. So if we get our begin time here, we're ensuring that any interrupts or anything that happens too will also be recorded by our game, just so that we can detect lag spikes and stuff like that. Now this begin time, end time, dt variable, they're all kind of useless if we don't have an actual update loop. So we need to start our scene manager so that we can have some update loops. So let's go into here, and what we're going to do is we're going to create this class called scene. And so this scene class is going to be abstract because It's going to implement a couple methods that we would like it to implement. And for now, what we're going to say is public scene takes in nothing. So it's just simply a empty constructor. And eventually this is going to have a whole bunch of things. It's going to have the game objects, the render, the physics handle, all those different things is going to be contained within this scene class. And so it's going to be sort of, like I said, our big game wrapper. And then what we're going to do is we're going to create an abstract method. So public abstract void update. It's going to take in a float delta time. And so this is where we're going to pass our update method. And then it will go into this scene and update whatever it needs to update. Now we're going to go into here, we're going to create a new class called level editor scene. So this is going to be our level editor scene where we're actually editing levels, and we'll have another scene called level scene where we are playing the levels. So hopefully that's pretty self-explanatory. And level editor scene, once again, we're just going to initialize it and create the initializer with nothing in it for now. And then inside of here, we're going to implement that abstract method. So up here, we'll say this extends our scene object, and that's going to say you need to implement that method. So I'll hit Alt Enter and we will implement that method. Now we can use this DT variable, so we can update according to delta time. And so now we're going to use this to transition from level editor scene to, and then we will go create another scene, level scene, and we're going to make it fade to black over 2 seconds. And I'll show you how you can change that and stuff too. So we're going to create this level scene, also an empty constructor, and this is also going to extend scene. And so these are going to be like the two main scenes we're going to have. I had one other scene called test scene that I didn't really end up using too much, so we'll think about adding that because it might be nice if you want to keep some code around, which is what I used it for when I was testing things and stuff. So now we have this scene, we have this test scene, and we have we have a level scene and level editor scene. Let's go to our window, and we want our window to be able to change between scenes. So we will have a private static scene variable, and this is going to be the current scene. And we're going to initialize this to null. And actually, let's make this an integer. So it's going to be an integer variable. And then we'll just initialize this to -1. So then we're going to have a public static method in here, void, and it's going to be called change scene. And we're just going to take in an int variable, and this is going to be the new scene, the scene that we want to change to. Then we will switch on that new scene, and we'll say case 0 will make a new level editor scene, and I'm going to say our current scene equals new level editor scene. And we will make this a private static scene variable. And then we'll just call this current scene index, because actually we don't even need this one. Yeah, we'll just have a current scene. I'm sorry. Trying to just write this from scratch. So we'll just have our current scene, and then we'll have this integer which tells us which scene we want to switch to. So then we'll say current scene equals a new level editor scene. I feel like I'm spelling these wrong. I don't know. It just looks really weird now. I think that's right, but if it's not, then that was an accident. So then we'll say current scene dot update, or init or anything like that that you would have happen, you would do right here, just so that we have that working, and then we'll break. Then we'll say case 1 current scene equals new level scene. And then once again, you would do your init or anything like that. And then for our default case, we'll just assert false, and we'll say unknown scene. Now this isn't going to do anything, and then we'll just say like plus the scenes index that we're trying to pass in. This isn't going to do anything yet because we don't have assertions enabled, but we will enable assertions, and this is how we will do this because it's actually really nice to have these in our game. So we have all these different things, and then let's go into our level editor scene, which is where we're going to be starting. And then inside our update method, we'll say if input, if key listener dot is key pressed, and we're going to say key event dot vk space, and then we're going to say if not changing scene, and we press the key. Then up here we're going to add in a Boolean variable, which is going to be private Boolean changing scene equals false. And then inside here, we're going to say changing scene equals true. So if we are changing the scene, then we want to slowly decrease the opacity, just like we did in the color to black, so that it fades. Then we'll say if changing scene. Then we will do another variable up here, which will keep track of how long it takes to change the scene. So float time to change scene. We can initialize that to 2 seconds. So this is how long it's going to take us. If changing scene and time to change scene is less or greater than 0, so we still have time left. And then we're going to say else if changing scene and the time to change the scene is less than 0, that means that we've finished fading and now we want to actually change the scene. So we'll say window.change_scene to 1, which will change us to the level editor scene. And then inside here, what we're going to say is time to change scene minus equals dt. So we take away the time that's passed in the last frame. And then we're going to just update the Windows RGB. So we're going to say minus equals dt times, we'll do like 5.0f window.get.r or g minus equals dt times 5.0f. And then window.get.b equal minus equals dt times 5.0f. So this may not fade exactly perfectly, but it will give us the 2 seconds that we're looking for. Let's go to our window real quick, just make these public right here, just so that we can access them for now. This is not how you would do it normally too. This is not the best way to do it, but it's whatever. And then let's take out this key event that we were handling inside here. So we'll take out the fade to black thing. And then right down here is where we're going to update using our DT variable. So let's actually initialize our DT variable out here. We'll say float DT equals 0.0f. Actually, we'll make this negative 1.0f. And then what we're going to do is check and see if we've actually done a frame yet. And so right here, we will say current scene dot update DT. And then right here, we will not duplicately initialize this. And then right here, we'll say if DT is greater than 0, greater than or equal to 0, we will update. Otherwise, we won't. So that way, when we first go through here, we do not update because there's no time, right? DT gets initialized down here. And then next time we go through, we get the actual DT, and then we can update our scene. So it's like a lag of 2 frames. We're not actually going to start updating our game until 2 frames later, which is fine for now. If it becomes a problem, we can check and see how to fix that. Now let's go into here, and then we'll just say system.out.println inside level editor scene. And then we'll go into our level scene, and we'll say system.out.println inside level scene, just so that we know if it is working and we are switching scenes. So if we start up our game, we're going to get an error here. And current scene is null. We never changed our scenes. So what we have to do is after we initialize everything right down here, we should say window.change_scene 0, just so that we make sure we are in a scene before we actually start our game. There we go. And then we get our window. If I hit space, it fades to black. And then after about 2 seconds, it should be white again. Actually, it might not be white again because we're not changing the color on change scene. But if you look down here, it says we were inside level editor scene, then inside level scene. So we did change scenes. And then what we can do is inside level editor scene, or level scene. Once we initialize, we'll say window.get.r equals 1, window.get.g equals 1, window.get.b equals 1. And now that should give us a white screen once we switch scenes. And if we wait, and then it changes back to white. So we now have a successful scene manager and a window that can handle the changing of the scenes. And we have our delta time variable, which is working as we would expect too. If you want to see how many frames per second you are running at too, like I said earlier, you can just print out 1 over dt, which should be your frames per second. So if we go down here, we can say print line, and then we'll say we are running at, we'll just do that plus 1 over dt, and make sure this is a float, because otherwise you will be doing integer division, plus FPS. And if we run this one more time, we should see about how many frames per second we're running, which is going to be pretty ridiculous. because we are not currently doing anything right now. And so then if I go, oh, actually, that's actually pretty normal. So 59 frames per second typically, and then 119 frames per second. And this is actually a good point too. The reason it's so uniform, which is really good too, we want it to be uniform, is because it's locking to the refresh rate of our monitor. So if we go back into our window, remember, we did this whole swap interval 1 thing, right? What this does is it locks our frame rate to the interval of the refresh rate of our window. GLFW does some stuff underneath the hood. That way we get a pretty uniform frame rate. Now, you get some spikes down and up, but for the most part, you are running at a solid 60 frames per second or whatever the refresh rate of your monitor should be. So we can now see how many frames per second we're running at and stuff too. All in all, what we did is we simply added in the scene manager. This whole changing scene isn't too important. The scene manager basically has an abstract update method so that each scene can do different things in the update method. And then the window can change the scenes now just by going and getting this method called and then just literally instantiating a new scene of the specific type we want it to instantiate. And then delta time is literally just getting the time when the scene starts, which is down here, and then getting the end time and getting delta time, which is the time that it took to get from here all the way back to here. So that's all that's happening. If anything doesn't make sense, leave a comment. And the next tutorial, what we're going to start going over is probably some like drawing stuff. Now, we won't be drawing anything to the screen, but I'll be going over how drawing works in OpenGL and how we're going to sort of get that up and running because it's quite a bit of stuff. So in the last tutorial, what we did was we went over scene management and the delta time variable in the game loop. So I would highly suggest you check that out if you haven't. In this tutorial, I'm going to be purely explaining there is going to be no coding, but it's super important, especially if you've never done any graphics programming on the actual graphics card. So what is programming on the graphics card? Why is it so hard? What is it like? Well, it's actually a lot different than programming on the CPU using high-level languages. You have to use a lower-level language, and there's a whole pipeline that it goes through. And in order to understand why it's so difficult, we sort of have to take a look at how we send data to the graphics card and how it gets processed. So that's what we're going to do today. We're going to do a high-level overview on the entire stages of the graphics pipeline. This is going to be mostly taken from the OpenGL tutorial Hello Triangle, which I will have a link to in the description. And in case this is not clear enough, I will link some other videos by Thin Matrix because he has some really good explanations on this stuff too. So just in case you want some further material, there will be links in the description that you can check out below. So let's try and see how all this stuff works. Before we take a look at how things are done today, I think it's important to look back on history and see how things were done initially. Now, back in the 80s and 90s, we had this thing called raster graphics. You may have heard of this term. It's really simple. All it means is basically that the screens were fixed width and height, and so they stored the amount of pixels in a flat array like this, with the RGB for the first pixel, RGB for the second pixel, so on and so forth, going across the screen, and then they would blit the image, B-L-I-T, which means they would just basically copy this buffer straight to the screen. They didn't have to worry about really stretching it too much because the screen size didn't vary that much. Say, for example, you were creating Mario, they knew they were creating it just for the SNES or some other system. The most they would have to do is just stretch the pixels, which was done by some internal tools, typically done on the operating system. So they would just have a fixed size of pixels that they would blit onto the screen. Raster graphics, pretty simple. Today, however, things are quite different. The reason they're different is because of the move to 3D, first of all, and the move to using graphics cards, which uses this 3D stuff. So the way that 3D works is it goes through a whole pipeline that we have to sort of program a few parts of and send all this data to the GPU. So I have the pipeline here, which is taken pretty much directly from that tutorial too, which you can find more explanation in detail on the website. It is written for C++, not Java. But basically, the reason that we have this whole shape assembly thing and stuff too is because in modern GPUs, you don't send pixels, you send shapes. And so typically these shapes are triangles. So in our case, what we'd want to send is a bunch of squares since we're sending all sprites and 2D stuff to the GPU, right? So we're going to be sending in these lists of vertices. It's a whole different way of thinking. No longer thinking about pixels, you're thinking about vertices. So this would be like V0, V1, V2, V3. And the way that the graphics pipeline works in modern technology is it first goes through a vertex shader. This is something we program. The vertex shader transforms these pixels, these coordinates into normalized device coordinates. So basically, you have your world coordinates, which is some points in 3D space and stuff, which makes sense to you. And then what you do is you multiply it by some projection, which is basically like the size of the screen that you're on and everything and the dimensions. And then it transforms these coordinates so that they are now in a range that is normalized for the computer. And we'll take a look at more what that means in a second. Next stage, the GPU does this automatically. So we write a shader for this. We have to handwrite this one. Shape assembly is done automatically by the GPU. All it does is you can tell it stuff like GL line, GL triangles, or GL strips. Or I mean points, I'm sorry. So line is actually strip, and then you have GL point. And so these three different flags basically tell the GPU, hey, I'm sending you a bunch of points. This is how I want you to process them. So if you have triangles, it's going to assemble them into triangles. If you have points, it's just going to leave them as points. And then if you have strip, it's going to turn them into like lines. So this is actually strips. Next, what it does is it goes through something called a geometry shader. This is something also programmable that you can do yourself, but most people don't because there isn't really much use for it unless you have very specific use cases. The only thing I can think of where it kind of makes sense is say you have some like 3D ocean. And so you know that they move over time and the waves move. And so a geometry shader basically allows you to add geometry to add more shapes. And so maybe you want it to move like noisily and actually move up and down and create more geometry or something. It's just, there's not a lot of use cases for this. So what you see here is sort of an example of how it could have been used. This point got added and now you have two triangles instead of one. So geometry shader allows you to make more shapes. Next phase, it goes down here to rasterization. So you'll recognize that because of our raster graphics. This is the process of converting these abstract shapes into pixels. And so the GPU does this automatically too. And it basically turns all of the stuff that we have passed it into pixels appropriate for the device that it is drawing to. After that, it goes through the fragment shader. This one is another one that we can program and that we have to program. So the vertex shader and the fragment shader are going to be our primary sources of concern because these are what we have to program. The fragment shader is in charge of coloring every single one of those pixels. So you can define basically a way to color all the different pixels that you now have. And it will pass them to you in sort of weird way. We'll take a look at a couple of these programs so we can explore a little bit more about how they work. But basically what you would do in this shader typically is lighting calculations, any sort of like cartoon shaders or something like that you have, PBR rendering, all that stuff is done in the fragment shader typically. The last stage is tests and blending. Now, we don't have to write this explicitly, but we do have to tell the GPU a little bit about what kind of blending we want and the tests we want. Say you have an object that is in front of another object. This is the part where the object closest to the camera would stay, and then GL would blend between this and the one in the back. So if it was a solid object, then it would just clip the object behind and only show the object closest to the camera. If it was something like glass, then it would blend between the light color. So then, like you had red stained glass, it would make it sort of a reddish tint for the object behind it to give it that glass look and feel. And so that's sort of what the blending is and the test. Also, the clipping happens in the shape assembly stage. So if there's anything lying outside of the screen, they get clipped from this whole thing. So because now you have them in normalized device coordinates, so you can tell what is inside and what is outside, just so that you know. Now I talked about normal device coordinates and vertex shaders. What normal device coordinates are is it's basically just defining the screen from -1 to +1. -1 is left side screen, +1 is right, -1 is bottom of the screen, and +1 is the top. So normal device coordinates. It's basically just so that it's easier for the graphics card to make all these calculations and stuff since they are in that normal range. Now, vertex shaders expect, remember we said that we have to think about things in terms of vertices. They expect an array full of vertices. And so what I have here is something called a VBO, or a vertex buffer object. This is something that we define, and it's basically our collection of vertices. Now, vertices can have many things attached to them. They can have colors, they can have texture coordinates, and all sorts of stuff. So this could be a red pixel, this could be a green pixel, this could be a blue pixel, and this one could be a black pixel. And basically what the GPU expects is, okay, if we want to send all this data with our pixels, then we have to encode it into the array directly. And so basically what our VBO will look like is we'll have our position in the x coordinate, our y position in the coordinate, and z position of the vertex. And typically you will have a bunch of attributes that you define yourself. So I have RGB and TX, TY for texture coordinate x and texture coordinate y. You do not need these. These could be defined as anything you want. So I actually have some shaders where I use some very specific attributes that I define myself. That's what each of these are called. This is a position attribute is what we could call it. This is called a color attribute, and this is called texture attribute. And now we also have to define to the GPU a couple of these terms. We have to define the offsets of each attribute. So we would say, oh, our R color, that's 3 offset from the beginning of the vertex. And then we have to identify the stride, which basically tells the GPU, this is how long you have to go between each vertex. And so the stride would be 8 since there's 8 things in there. And I believe this is in bytes. So if you had like floats, then you have to do 8 times 4. And we'll explain more of that once we go into the code. But that way, basically, so the GPU knows, oh, if I'm here, if I want to get the next attribute, I have to go 8 out. And then it knows it has to go somewhere out here. And it can calculate between each attribute and between each position, everything. Now, there are a few other things that we have to send to the GPU. If you think about each of our sprites as a single square, then how do we group these squares together in a way that makes sense to the GPU? How do we make sure that each of these is like one object, right? So this is one picture on our screen. We want this to be one object. Well, the GPU has these things called VAOs, which are vertex array objects. And so basically these define sort of the attributes and the vertices. So this contains all the information about, okay, this is the VBO I'm using first of all. Then it tells you, hey, okay, this is where attribute 0 is. So this is where the position is. And then you sort of tell it, hey, the stride is this, the offset is this. Then you say, hey, this is where my attribute 1 is. And the stride is this, the offset is this. And the VAO will contain all that information. Now, another thing you have to consider, what if you want to draw these 2 triangles? Well, you could do it 2 ways. You could go, here's the first vertice, here's the second vertice, here's the third vertice. That's the first triangle. Here's the 4th vertice, here's the 5th vertice, here's the 6th vertice. That's the second triangle. Now you'll notice we just duplicated 2 of those vertices, which is really inefficient in memory and wastes time in general. What you would like to say is, here's vertices 0, 1, 2, and 3. I would like you to draw a triangle from 0, 1 to 2, and from 0 to 3 to 1. And the GPU lets you do that. So you just have to specify one more buffer object. This is called an element buffer object, or EBO. And basically what it allows you to do is to define these coordinates, or these indices, which define which vertices you're using. So you can go, hey, I want to use 0, 1, and 2. Then the GPU would go, okay, let's look into our VBO. Here's vertice 0. Here's vertice 1. And then, oh, here's vertice 2. And so then it would use this, this, and this. Then it says 0, 3, 1, and so V3 would be somewhere out here. And it would be like, okay, I'll use this vertice, and this vertice. And it allows it to index directly into the array and figure out which attributes you want to use. This is really helpful because then, like I said, you're not duplicating these vertices anymore. You're just saying, just use the ones I already have because we don't need to duplicate those. Then you can create as many VAOs as you want. So say you wanted another square, you could create another VAO. Now this is actually quite inefficient, and we will do a smarter way than this, because if you create more VAOs, that creates more draw calls, which ends up lagging your game a lot more. So we'll figure out ways to group it so that we can have 2 squares in one VAO, which I hope you can begin to see how you might do that. And then we can just have one draw call, which speeds up our game tremendously. So we'll look into that in a future tutorial called batching. Now we have to take a look at the thing called fragment shaders. So what are fragment shaders exactly? Well, they sort of define the way that the pixels look on the screen, right? They define the colors. So basically, say you had a square on your screen right here. If we zoomed way in and took a look at each individual pixel, you can sort of think of the fragment shader like a big parallel processed program. And basically you have a program running for this pixel, for this pixel, for this pixel, for this pixel. You have a program running for every single one of these pixels at the same time. And that's essentially what the chipset does. That's why it's so much faster, because instead of having to go and loop through every single pixel, you can do a whole bunch of pixels at the once, because that's what the GPU is made for. And so you basically have a program running for every single pixel, and you have to think about it in terms of not, okay, I want a color red here, green here, blue here. It basically changes and it interpolates. So if you have a red pixel here and you want a green pixel here, what it's going to do is it's going to interpolate between these two and give you a gradient from red to green throughout here and basically use those colors. And it does this automatically. It's very confusing. This is one of the hardest parts of shader programming that I think is to grasp is fragment shaders, because trying to think about this in this way is completely different. There's a great website called Shaderbook. I think it's Shaderbook. I'll have a link to it in the description. And it's really great if you want to learn more about shaders and how they work and stuff. It uses a slightly different language than we'll be using, but that's fine because the concepts are really what the hardest part of this is. In the last phase, we have to do manually. So as I said before, there's a lot that goes into this. So we've basically defined to the GPU, hey, we have this vertex shader, we have this fragment shader. Hey, GPU, we have this VBO, this VAO, this EBO. We want to send all this data to you, and we want you to draw it. And so then the GPU is like, okay, cool, but how do we tell the GPU which vertex shader and which fragment shader to use and all that stuff? Well, we have to do this thing called compilation and linking. And if you don't know what compilation is, it's basically taking a high-level language like Java. So you have some Java syntax, if true, blah, 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 do, well, actually that'd be a bracket, do, blah, 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 which the computer cannot understand. And Java actually compiles it to some bytecode where it would be like JMP if false to register 32 or something like that. And then this actually gets compiled again to machine code, which is just a bunch of zeros and ones. And then the computer can run this. And so compilation is basically taking something that looks like this and taking it all the way down to that machine code where we can understand it. So we have to do this manually for our shaders. And so we have our vertex shader, which is a program we wrote. We have our fragment shader, which is also a program we wrote. What we have to do is we have to tell OpenGL, hey, compile this and compile this. Then we take our compiled output and we say, hey, okay, these two shaders are linked together. We need you to link this executable code that we have generated for the GPU and this executable code that we have generated for the GPU. This is our fragment, this is our, this is our fragment, this is our vertex. Link them together so that they know how to find each other. And we have to do all that manually. And then and only then we can use these shaders, and we can use them in conjunction with a VAO. So you can actually use one shader for any amount of objects, any amount of VAOs, and then you can use a different shader for those same VAOs. So the cool thing about this is you can change the entire look and feel of your game by just changing the shader. And that will change every single object in your game, because the VAOs are basically just our objects in memory. They're just our squares, our sprites. And so you can just use any shaders you want with these sprites, and it doesn't matter to the GPU. It will do the same steps on them no matter what they are. So high level overview. I want to take one more look at just a shader real quick so we can sort of look at them and see how they work. So let's take a look at a fragment shader and a vertex shader and see some of the concrete stuff that they might do. What I have on here is a couple of shader programs. So you can see the top one is a hashtag type vertex program, and they're in the same file. And then the bottom one is hashtag type fragment shader. So this is our fragment program, and this is our vertex shader program. And so basically what these are sort of definitions to the GPU of how we want to do these things that we talked about in that little bit about how these things work. So remember I said for the vertex shader, we have these things called VBOs, right? And they have these attributes that we attach them, 0, 1, 2, 3. Now each of these attributes points to some position in that array. So basically what we're saying here is we're getting some array that we already defined. where the position is defined as the 0th attribute, the color is the first attribute, the texture coordinates, second attribute, and the texture ID is the third attribute. And so those would be defined just sort of as that whole stride offset thingy. We'd be like, oh, offset of 0, offset of 3, or whatever we have to do, offset of whatever this one is, and oh, the stride is however big each of these vertices are. And so we get all those passed in as these variables. Then we also define some variables that we're sending out to our fragment shader. So typically, the shaders go vertex to fragment, and you can send data between them. So you can say, okay, I want to send this data to my fragment shader, which is why we have to link them together. Then we have these things called uniforms, and these are a little bit different. They're like global uploads. So basically, you can say upload a variable and just upload it to whatever shader is currently being used. And we'll talk more about these once we actually get into uniforms and shaders specifically. Now we have our main function, which is what is automatically called from the GPU. And basically it expects a GL position to be returned. Notice GL position is not defined anywhere up here, but it's just automatically inferred to be returned by our shader. So we use some of those variables that we had up there and sent the out variables to some of the variables we got in. And then we basically transform from world coordinates to normalized device coordinates right here with this multiplication. This is actually matrix multiplication. So it works a little bit different than normal multiplication, and it works with linear algebra. I can do a primer on that if we really need it. But basically all it's doing is saying, hey, the out position is going to be normalized device coordinates from our world coordinates, which were passed in up here in this A pose. Then it all gets passed into the fragment shader. And so the fragment shader is that big parallel processed unit that operates on every single pixel. And so basically we have some more of those uniforms, and then we have some of those variables that we got passed in from the out variables here. And so they're the same name, and that's sort of how GL translates them and finds them and everything. And basically I've made this one pretty simple for the first fragment shader. It's just a texture sampler. And so all it's doing is it's sampling the texture. Right now it's not actually sampling it from anywhere good. We're just setting the color here. And then what you would do is you would say, oh, text color equals texture sample. And then you would pass it in the f text chords .x. Actually, you could just pass it in the f text chords. And so basically what this does is it sets it to the texture of whichever pixel we're on. So say we had a 32 by 32 pixel. What this would do, because remember, these are passed in the variables sort of interpolated. So if we were in the middle of that picture, what it would do is it would have an interpolated value, not the actual value that we're expecting. And it would sort of pick a pixel in the middle of that picture and then set the color to whatever the color of that picture was on our actual screen. It's confusing. It's really complicated. Like I said, there's going to be additional resources to sort of understand this stuff a little bit further. And once we actually start coding these and seeing how they work, hopefully you'll begin to see how they work a little bit better. But check the description for more resources if you want that. And we're going to try and code all of these concepts tomorrow by drawing a triangle to the screen. Actually, probably a square. Drawing a square to the screen, using every single one of these concepts to see how it all works in action. And that's going to be quite a big task, but we'll get it done. In the last tutorial, what we did was we went over how to program a GPU, the high-level abstract concepts. In this tutorial, we're going to be employing all those techniques, so it's really important that you see that before you do this one if you've never done any graphics programming before. So what we're going to be doing is drawing a square to the screen that has a nice gradient going from each of the corners. So we're going to be drawing this using vertex colors, which means we can assign a color to each of the vertices, and then we're just going to be drawing it to the screen. So it's going to be a little bit hard. There's going to be a lot of new stuff, but if you've seen the last tutorial, hopefully it'll have prepared you sort of for what is about to come, and you'll be able to understand it as we're going through it. Okay guys, so let's do that real quick. Alright guys, so we're going to start coding now, and we're going to do quite a few things to get this square up onto the screen. So first thing I'm going to do is remove this sort of temporary code we had in the level editor scene. I'm just going to delete all this. It was sort of just a proof of concept to make sure we knew what we were doing and how we could use all the different things that we were starting to use. Next thing I'm going to do is create an init method, because we're going to need that eventually. So let's go into our scene, and we're going to create a public void init that the scene can override if they would like to. And then inside window, like I said before, we are actually going to initialize now. So I'm going to uncomment this and then copy it down to here so that all scenes are initialized before they are run. So we can see when we change a scene, we create the scene, which calls the constructor, then it initializes, and then it calls run on the scene as the very last step. Next thing we're going to do is go back into our level editor scene, and we will be doing some stuff in here in just a moment. But before we can, one of the main things you need in order to draw things to the screen using the GPU is shaders. Shaders sort of describe the way that it needs to be drawn to the screen. So we're going to build a super simple shader that will literally just put what we give it to the GPU and display it on the screen. So I'm right clicking up here at the project root, and I'm going to hit a new directory, and I'm going to call this assets. And then inside this assets folder, I'm going to do another new directory and call this shaders, because shaders are assets in my mind in this, because they're a file that we have to load. So then I'm going to do a new file and call this default.glsl, which is GL's shader language. So that's what it stands for, Graphics Library Shader Language. I'm going to add this to Git. If you were doing version control, I would recommend doing that too. Now I have a syntax highlighter for my shaders, and if you want to do that, hit Control-Alt-Shift-S, and actually that's the wrong one, sorry. Go to File and then go into Settings, and you'll see this thing called Plugins. The plugin I have for this shader is called GLSL Support, and it just highlights my shaders for me. You can install it just by going to Plugins and then searching here, and it'll pull it up for you. This I'm not going to explain too much about. These are very simple, and we're going to go into more depth about shader language and everything once we actually talk specifically about shaders. But since this is just a means to the end for this video, we're just going to sort of go through it. So this is just decoration for us later on in the series. This isn't actually a part of the language feature. So this is actually nothing to do with shaders. But I'm going to say hashtag type vertex version 330 core, which is my GL version that I'm using. And then we're going to do layout location equals 0 in vec3, and I'm going to call this a pose. I prefix my variables in shaders with letters so that I know what they stand for. A is an attribute, so I know that anything starting with an A is an attribute, which we also know because it's coming from this layout location. Next, we're going to say layout location equals 1, and this is going to be in a vec4, and this is going to be our A color. So this is sort of the attributes we're going to define. We're going to define a position and a color that we will send to the shader. Next thing we're going to do is have a variable that we're going to pass to the fragment shader. And we're going to say out vec4 f color. And so I prefix it with an F for fragment because this is going to the fragment shader. Then all shaders have a main function, so we can just call that right here. We'll say void main. And we're going to say f color equals a color. We're just going to pass the color to the fragment shader. And then we're going to say GL position, which is just a variable that is always there and that we need to define, is a vec4 a pose 1.0. And what that means, it's going to create a vector 4 using this as the first three parts of that vector and 1 as the last part of that vector. Now I'm going to say hash type fragment. Once again, this is just decoration so that we know. And then we're going to say hashtag version 330 core, same way we started the vertex shader. This is now our fragment shader, everything from this line down. And we're going to say it takes in a vec4 f color, and this is important. If you forget this, it's going to say there is an error because we have an out vec4 color here. We need an in here to the fragment. Then we're going to say out vec4 color. This is sort of our user-defined variable that says, hey GL, this is the color we are outputting. And we'll say main void main, because all fragment shaders have a main function too. We're just going to say color equals f color. So literally all this is doing is we're giving GL the position that we passed in, and then we're passing the color from the vertex to the fragment shader, and it's just coloring the square of that color. So nothing too complicated in the shader. Once again, like I said, we'll go more into depth about how shader language works and more stuff you can do with it, but this is all we need for now. So now that we have our shader source, let's go into our level editor scene, and we're going to create two variables up here. Actually, let's just make these private. So we'll have a private string vertex shader source, and this is going to equal some string, and then we're going to have a private string fragment shader source, and this is also going to equal some string. And then if we go back into our shader, copy everything for the vertex shader, everything from the version 3.3 core down to the bottom of the main function, And then if you just go back into your level editor scene and copy and paste it here, IntelliJ formats it for us, which is really nice. Puts in all the pluses and the /n's, super cool. Go back into default, GLSL, and then copy this, the fragment shader, and then we'll go back into level editor scene and paste that right there. So now we have our fragment and our vertex source strings, and we're going to need a couple more things so that GL can identify them. So since we're passing data from the CPU to the GPU, we need sort of identifiers so that we can know what we're working with when we're talking to the GPU. So GL gives us these things called IDs for identifiers so that we can identify what we're working with. So we have identifiers for the vertex, the fragment, and the shader program, which is the combination of the vertex and the fragment source. So the next thing we're going to do is we're going to actually set these. So we'll go into here and we will override that init function that we just created. So we'll make a new initialization. And inside this initialization, what we're going to do is first we're going to compile and link the shaders. And this is actually pretty straightforward, but if you don't know the functions, you have no idea what's going to happen. So first thing we're going to do is load and compile the vertex shader. And we do that by saying vertex ID, the identifier we want, is GL create shader. And we're going to pass it the GL vertex shader to tell GL this is a vertex shader. Hit Alt-4 over this and then just hit import static constant. And just make sure you do the GL20 without a C or 30, whichever one you have, it's fine. And then I'm going to import that one as well. Next, we want to pass the shader source code to the GPU so that it can compile it and everything. So we will say GL shader. This is actually probably not passing it to the GPU. GL is doing something under the hood that's just sort of making sure everything gets done properly. So we are going to send it the vertex ID. This is the shader we want to pass the source for, and we're going to pass it the shader source. So we're saying pass in the shader source to that ID, which is the shader we just created up there. So right here. And I'm going to do that and hit Alt-4 and import that. I did that wrong. There we go. Then we're going to say GL compile shader. Vertex ID, the identifier we want to compile. And that's pretty simple. Now we want to check and see if there were errors, because if there was an error, we're not going to know about it unless we look for it. So we're going to say check for errors in the compilation process. And we're going to say int success equals GL get shader I, which stands for info. So get shader info for our vertex ID, and we want the compile status. So we're going to say GL compile status, which will give us a 0 if it did not succeed, and a 1 or something else, something non-zero if it did succeed. And so we'll say if success equals GL false, which is just a 0. If you control over this, you can see it says GL false is just 0. So if we did not succeed, first we have to get the length of this string. And this is because of some of the things, right? Like I said, we're going into C a little bit here. And so C is very verbose when it comes to strings. You need the length and in order to just display the string. So we'll say get shader I for get shader info. And we're going to pass in the vertex ID. And we're going to ask for the GL info log length, which will give us the length of the info log. Then we'll say system.out.println error default shader.glsl is the file that we had the error in. And then we're going to do a new line in a tab and say vertex shader compilation failed, just to give ourselves, what is happening here. Then we're going to say system.out.println, and we're going to say GL get shader info log, which will get us that info log, and we're going to pass in the vertex ID and the length because it needs both of those in order to do it. And I'm just going to say assert false and an empty string. And what this is going to do is it's just going to break out of the program. But I think you do need to enable assertions in order for that to work. And I can't exactly remember where that is. I will mention that in the next tutorial, how to enable assertions. But it will work once you have it enabled. So next thing we need to do is load the fragment shader and compile. Literally the same exact thing as this, except for fragment shader. So I'm going to copy all that, paste it right here. We're going to call this fragment ID, copy fragment ID, and paste it everywhere you see vertex ID. and we no longer want to declare this as a new variable since it's not. And then we want to go up to where we create the shader and just make sure we tell it it's a fragment shader, not a vertex shader. And make sure you pass in the fragment shader source instead of the vertex shader source. And that should be good. So now we have compiled and checked for errors for the fragment shader too. Now we want to create the actual program, link it, and that should be the rest of it for our shader work. So we're going to say link shaders and check for errors. Very similar to what we just did up there too. We're going to say shader program equals GL create program. So once again, we're creating a new unique identifier for our program. And we're going to say attach shader, GL attach shader, shader program. We want to attach the vertex ID to our shader program. And we want to attach the fragment ID to our program. And then we'll say link the program. And we'll just pass it the program. So now we've attached both shaders and we're saying, okay, now link it together. And next we have to check for linking errors. So we'll say success equals GL get program I, so get program info, shader program, and GL link status. So we're looking for the link status, not compile status now. And once again, if success equals GL false, then we had an error. And we'll say int length equals GL get program I. And we're going to say shader program instead this time. And GL info log length once again. Then we'll just say copy all this stuff real quick and paste it right here. And also change this from vertex to fragment because this is when we were compiling the fragment. So we do want to make sure we're accurate when we're displaying the errors. And then we'll say right here, instead of vertex shader compilation failed, we'll say linking of shaders failed. And then we will get the shader, the program info log. So not the shader info log. So say get program info log, and we'll pass in the shader program and the length, and that should be good. And then assert false and just break out of there. So all of this will compile and link the two shaders that we defined up here, which is good. If you run it, you should get no errors. And if we look down here, you see there were no errors. And then say, for instance, you misnamed this. You said in is a vec4 color. And then we can run this one more time. It says error default shader. If you click up here, it shows you the full error. And then we'll notice it says error default shader.gsl fragment shader compilation failed. Undefined variable f color. And you see it was expecting that f color variable because we passed it out of the vertex shader. So you can just change that back. But that shows that our error checking is working and it will notify us if they are. And you can also tell that assertions are not working because it didn't break out of our program, which we will fix in a little bit. Next thing we're going to do is we're going to create our vertex array, our element array, and our vertex attribute object, which is those other things I talked about in that last tutorial. So first we're going to go up here and we are going to say private float vertex array equals, and we're going to create a vertex array right there. And then we're also going to have private int element array equals, and we're going to do this right here. And so for our vertex array, the way I want it to be is I want our vertices first, or our positions. I'm going to change that. And then our color second. So this should be position and then color is the way we want to format it. So we have to pass these in normalized device coordinates. Remember, -1 is the left side of the screen, +1 is the right side of the screen. So if we want a square, what we're going to do is we're going to say 0.5f minus 0.5f, 0.0f. We have to pass in as x, y, z. And this is going to be the bottom right, sorry. And then for the color for the bottom right, what I'm going to do is I'm just going to do 1.0f, so red, and then 1.0f. And then let's just leave a comment to ourselves. This is the bottom right. So next thing we're going to do is we're going to do minus 0.5f, 0.5f, 0.0f. And this is going to be the top left. And I'm just going to do this one as green, right? So RG, and then this one is B for blue. And this will be our alpha eventually. It's actually not going to work right now. So this is going to be our top left. And next vertex we're going to do is 0.5f, 0.5f, 0.0f. And we're going to call this one just the last color we have, which is blue. And so we're going to say this is the top right. And then lastly, we have to get the bottom left vertex for our square. So we're going to say minus 0.5f, minus 0.5f, 0.0f. And I'm just going to make this one that's red and green. So I think that will give us a yellow. And we'll say this is the bottom left. This is important that we know what we're doing here too, because we do want to be able to tell if we are actually getting the right colors that we're expecting, which we'll check in a second. I'm just going to format these so that they're all lined up the same. Okay, so that's our vertices, our vertex array. This, as you can see, we have position, color, position, color, position, color. That's the format that we are going to be expecting. Now for our element array, which basically says we want two triangles, the top right of the square and the bottom left of the square, and we need to define how these go. And it is important that you know this must be in counterclockwise order. So if we have a square, that's the top left corner, or yep, top left, top right, bottom left, bottom right, what we want to do is we want to make sure that we are going in counterclockwise order. So when we specify we have a triangle here with these three vertices, we must go this vertex, then this vertex, then this vertex. And then when we go here, we must go this vertex, this vertex, this vertex for the bottom left triangle, for the top right triangle. And to specify those, we can just look up here. We know which, so bottom right is 0, top left is 1, top right is 2, bottom left is 3. And then we can just use those indices to specify the order we want them to go in. So I'm going to say 2, 1, 0 for the top right triangle. And then I'm going to say 0, 1, 3 for the bottom left triangle. And if you do the indices in order of which ones these are, so this is 0, this is 1, this is 2, and this is 3, you'll notice that it goes just in the format that I specified, where we have the top right triangles vertices specified here and the bottom left triangles specified here. So that's our element array. Now we have everything we need to send them to the GPU. We have all the data, now we just want to actually send it to the GPU. So we'll go back down to our initialization function, and this is where we're going to be generating our VAO, our VBO, and our EBO buffer objects and sending them to the GPU. So we're going to need a couple more IDs actually. Let's go up here and we're just going to say private int VAO ID, VBO ID, and EBO ID for vertex array object, vertex buffer object, element buffer object. So go back down here. We'll say VO ID equals GL gen vertex arrays. And this is sort of OpenGL's way of creating a new vertex array inside the GPU and giving us that unique identifier once again. So we'll import that by hitting Alt-4. Then we'll say GL bind vertex array VAO ID. What this does is says, okay, everything we're about to do, make sure we're doing it to this array specifically. So make sure that everything that comes after this line is happening to this vertex array. So next we're going to say create a float buffer of vertices. We have to send a float buffer to OpenGL because that's just what it's expecting. So we'll say float buffer vertex buffer equals buffer utils dot create float buffer, and we're just going to pass in our vertex array dot length is what we want to do. So we're saying create a float buffer of the length vertex array length because that's how many we want to put into it. Then we'll say vertex buffer dot put, and we want to put our vertex array in there. And make sure you do dot flip because this will just make sure it's oriented the correct way for OpenGL. If you don't do that, it will throw an error and completely mess up. Okay, next we want to actually create the VBO, and we want to upload the vertex buffer. So vertex buffer. So what we'll do is we'll say VBO ID equals GL gen buffers. So once again, we're just generating a new buffer. GL bind buffer. So we want to say make sure everything we're doing is for this buffer specifically. And then we need to say GL array buffer because this is just an array, and VBO ID, that's the VBO, that's the ID we want to bind. So we're working on a certain VAO right now. We're working on a certain object, which is why we bound a vertex array. And right now we're saying, okay, now we're working on a certain buffer. Make sure you have this buffer in mind. Then we're just going to say GL buffer data, and we're going to say GL array buffer, vertex buffer, and GL static draw, which all this is we're saying, okay, we're working with an array buffer. This is the specific buffer that we want you to send to this ID. And we're only going to be drawing it statically. We're never going to be changing anything inside this buffer. So just make sure you use GL static draw. There is dynamic draw if you are going to be changing things, which we will use in the future. Next, we want to create the indices and upload. So the indices buffer, index buffer. So we'll say int buffer element buffer equals buffer utils dot create int buffer. Sorry. And we'll just say this is the element array dot length. Then we will say the element buffer dot put the element array, and we'll say dot flip. So literally the same thing we did for this one, except for elements. And then we're gonna do something very similar to this too, except for elements. So we'll say EBO ID equals GLGen buffers, generating a buffer for the EBO now. Say GL bind buffer, we want to bind the EBO now. This is an element array buffer. It's not just any regular array, it's an element array. So we need to make sure to specify that to GL. We'll say GL buffer data. We want to buffer the element array buffer, and we're going to send it to the buffer itself. And then we're going to say GL static draw. So once again, statically drawing it, we're sending it the buffer we just created, and we're saying it's an element buffer. Make sure you know that. Next, we need to add the vertex attribute pointers. So this is those things I was telling you about. How does the GPU know that we have position first, then color? Well, we have to tell it. How do we tell it? Well, we're going to find out in just a second. We're going to create pointers that say, okay, position is the first 3, color is the 4 after that. And then the total length of one vertex is 7. We have to specify all that. So this is where we're going to specify all that. We're going to say int positions size. So this is just how many positions there were, 3 XYZ. So position size is 3. Int color size equals 4. There's 4 colors, RGBA. Int float size in bytes is 4. So there's 4 bytes for one float. And if you notice, each of these is a float. We have to make sure to include this. We have to be very specific, very. And Java doesn't give us any nice way to know this offhand. You just sort of have to know that the size of a float is 4 bytes. And actually in C, you could do like size of, which will create a sort of implementation, just that we're not saying like, oh, we're just going to magically know this. We're going to actually create something that tells us that. Then we're going to say int vertex size in bytes equals the position size plus the color size times the float size in bytes. So we know that if we add these two, 3 plus 4, and multiply that by how big one float is, it'll give us how big the whole vertex is in floats. It's important. Now we're going to say GL vertex attrib pointer. So attribute pointer 0. We're going to say the size is position size 3. We're going to say we're passing in GL float. The type is a float. Normalized is false. Technically it's true, but we'll just say false. Doesn't matter really what you do for that. Okay, the stride. The stride just means how long till the next vertex. Well, that's 7, but we have to specify that in bytes. So we'll say vertex size in bytes. And then the pointer, we're just going to say 0. That's basically like the offset. So offset is 0 because we are not going anywhere to get to that point. Then say GL enable vertex attrib array 0. So we just enable it after that. Okay. Now we do the same thing for actually, let me real quick show you too. So 0, why 0, 0? Well, default.glsl. Remember, we said location 0, location 1. So location 0 is the position. And if you notice, we're saying at 0, we're putting the position. Then what we're going to say is GL vertex attrib array, or pointer, sorry, 1, and we're going to do the color, right? So the color size, it's also floats, false. And vertex size has not changed. And now the offset is actually positions size because we've actually moved the position size over. And I think that has to be in bytes as well. It does. So position size times float size in bytes. Make sure you do this so that it is in bytes and not just the size. So the offset is going to be 3 because there's 3 positions, times 4 for the size in bytes before we get to the first color attribute. And that's sort of what we're telling the GPU right there. Okay. And then next we're just going to say GL enable vertex attribute array 1, same thing we did just a moment ago. Now that we have initialized this, and sent our square to the GPU, we can finally draw it, which thankfully, you guys are probably thinking is actually pretty simple compared to all the stuff we just did. To do that, first we need to bind our shader program. We're saying, hey, we're using this shader program, so GL use program, and we're going to give it our shader program, which is our ID. Next, we're going to bind the vertex, the VAO that we're using, which is the VAO we defined up there. So GL bind vertex array, VAO. Oops, not VAO, VAO ID. So the ID of the VAO we just made. Then we're going to enable the vertex attribute pointers. So we'll say GL enable vertex attrib array 0, and then just copy that. Can't remember how to copy in IntelliJ. And then 1. So we enable 0 and 1, which are the ones we just defined right here. And then we say GL draw elements. We want to draw them as triangles, so we specify GL draw triangles. Then we say there are 6 of them, or we could say element array.length. That's how many indices we have, right? And then we'll say GL unsigned int is the type inside that element array, and we specified it as int, but I don't think Java has an unsigned int specifier. So int is good enough for us. We know they're never going to be negative. And then we're starting at 0, so we just put 0 there. Okay, and now that should draw the elements, and then after we draw them, it's important that we unbind everything. So we bound everything right here. Now we say unbind everything, which we do by saying first GL disable vertex attrib array 0 and GL disable 1. Then we say GL bind vertex at array 0, which basically says 0 is sort of a flag that says, okay, just bind nothing. And I'll say GL use program 0 to say, okay, use program nothing. And then that just unbinds everything. Now, if we run this, we should get a square. And look at that. It's exactly what we thought it would be. Green top left, blue top right, red bottom right, and yellow bottom left. If we go back up here, we said that the bottom right would be red, top left would be blue, top right would be green, and bottom left would be yellow. Exactly what we're getting right here. And if we change one of these colors, then if we like say top right should be purple, so I'll do a 1 right there, then we will notice the top right is now purple, pinkish. So that's how you draw things in OpenGL. Very complicated, I know. Pictures are just as complicated. We have to do a lot more to get a picture up on the screen, but we'll talk about that when we get to it. One last thing I want you to notice is the gradient. It's not just green up until we get to red. What GL does is if we go to our shader, the color that's getting passed in is actually based on the position within our actual object. And so it'll automatically interpolate and the color will slowly transition to whatever's on the left, the right, the bottom, and the top. There's ways you can change this if you want it to be a hard cutoff in each of the corners. But typically you actually want that gradient because it helps with a lot of things. So really cool, and you can actually make some cool effects with all that stuff. But that covers it for this tutorial. It was a long one. It was a lot of new stuff. If anything didn't make sense, please leave a comment and I will try and reply to that and may consider making a follow-up video because this is a lot of stuff and it's a lot of new stuff if you've never seen any of it before, and it can get very confusing. I hope it wasn't too confusing because of the previous tutorial, but I don't know. So I know this was super confusing to me when I first saw it. So in the last episode, we got our first square up onto the screen. In this episode, what we're going to do is start abstracting some of that stuff away so that we can easily configure this so that we can do a lot of different things with it. This one is specifically about shader abstraction. So what we're going to be doing is creating a shader class and then bringing all of that shader code out into that class so that it does all of it automatically. And all we have to do is specify where the shader is located on our system, and then everything will work out just like it should. So let's code that up real quick and get that nice and clean in our code base. Alright guys, so before we jump into the code, I do want to explain a concept that may be new to you because one of the things we're going to have to use is something called a regex, a regular expression. Now what these are, they're just glorified pattern matchers that allow you to look for very complex patterns and just sort of do different things with them. And in particular, what we're going to be doing is in our code, remember we have these things where we have like these identifiers and we basically have like a hashtag type and then we'll say like fragment. And then everything below this is our fragment shader. Then we have another string that's like hashtag type, and this one says vertex. And then everything below this one is our vertex code. And basically what we want to be able to do is Java gives us this thing called string.split, right? And so this allows you to split a string on, what do we want to split it on? This whole line is what we want to split it on. And so we can use these things called regexes, which allow us to match complex patterns that start with this and end with any text, is basically what we're going to want to say, because we don't know. The user could have a typo and spell fragment or vertex completely wrong, and we wouldn't know that. So how do we use these regexes? Well, in regexes, I'm only going to talk about a few different things that they can do. They can do a lot of different things, but the three main things they can do is the Claney star, which looks like this, which has a very close partner called the plus. I will explain all these in just a second. And then there's also the OR operator, which matches like A or B. And then there is also the range operator, which matches a range of letters. Okay, and so the way you can use this is, say you want to match the letter, any letter, A through Z. What you would do is you would do lowercase a through lowercase c, uppercase A through uppercase C to make sure you match lowercase and uppercase, and then bracket. And what this says is, okay, match anything that is in either of these ranges, except this is only going to find one character. So if your string is like something like A, B, C, D, it will only find this first one. So what you have to say is match, I want to match 0 or more, you would do a star. What this will do is it'll match the whole string up until it hits something that's not in this range. But you could also do something like, I only want to match it if there's one or more characters. And then what that would do is say, okay, I'll match it only if I have at least one character, and then continue going on. So that's what the plus does compared to the star. They're very similar. Then you could expand upon this, say, I also want to match numbers. So then you could do or 0 through 9. And what this will do is now it'll match any numbers or any characters. And you have to make sure you wrap these in parentheses to make sure that you can have numbers after characters too. And so basically the plus will now act on, okay, I want one or more any character or any number. And then that's basically the few that we'll sort of be using. And then you can sort of see how we can match something like hashtag type plus fragment. Well, what do we want to do? You can also match straight up strings. So we could say, we want to match hashtag type first. We know that's never going to change, right? So it starts with a type. Then we have one or more spaces. So we say plus, we want one or more spaces, at least one space, possibly more. And then we want any letter, any whatever they put, except for new line character. We can't do new line character. And regexes will automatically not check for new line character. So then we can just do our letter catcher, right? A through lowercase z, capital A through capital Z. And we say plus because we need at least one. And so then this pattern will match this whole line, and it will match this whole line, which will allow us to get our two things. And then we can split on this pattern. And what it will give us is it will give us this block of text and this block of text, which is exactly what we want. So that's just sort of a little prefix to what we're going to be doing. We will be using this exact pattern to be able to match those things. So let's jump into the code and actually code this thing up and see how it works. So if you remember, we left off with this giant function that does a lot of different things. But conveniently, we sort of broke it into pieces. So we have compile and link shaders, which goes from here all the way down to here. And so what ideally we would like to do is move all of this code into one shader class. So let's first go into our code, and then we're going to create a new package, and we're going to call this one our render, because this is going to contain all the render related code, which is exactly what a shader is. Then we're going to create a new class, and we'll just call this shader. So the way that I've developed this is when I get a shader, I want it to be really simple. I just want to be able to pass, hey, here's the file path, and then it does everything for me. It's like, okay, now we're going to figure everything out and do all that stuff. And then ideally what we would have is another function, which is compile. And this compiles the shader. So typically these two would happen very quickly one after the other. It is kind of nice to separate them because if you have an error in here, that's going to be different than the compile error. If we just have an error opening the file, we kind of want to know about that before we start trying to compile it. So that's the reason for separating them. And then the last one we want is a couple public void use and public void detach. And if you remember, some of the last things that we did inside of our level editor scene, right down here, we use the program, the shader program, and then we stop using it. So that's why we have all those different things. Now, back into this shader class. One of the things we need, remember, is a shader ID. So what we're going to do up here is we're going to say shader program ID, be a little bit more explicit this time, and this is a integer. And this will allow us to know that we're dealing with a what shader program this specific shader object is dealing with. Now, let's talk about opening up the file and stuff. It's really not that bad, but like I said, it's a little bit obscure how to do the splitting and stuff because of that whole regex thing. So it can get complicated, and I just want to make sure that it does not stay too complicated. Let's go up here real quick. We're going to store a few more strings because we're going to need the vertex source and the fragment source when we go to compile. So we will store those strings up there. And just for error handling and stuff, we will also store the file path. That way we can tell, hey, we had an error in this specific shader if we ever need to. So we'll start off, we'll say this .file path equals the file path they passed. And then we're going to do a try catch because in Java, every time you try to open a file, you need to make sure you're catching for an IO exception. And while we're on the topic of trying and catching things, I told you that I would talk about how to enable assertions. It's actually pretty simple. If you just go up to run, and then you want to go to edit run configurations. Oh, right here, edit configurations. And then inside of here, under VM options, you want to pass in a -EA. And what this does is it tells Java, hey, when you're running this, just make sure that you pass in that assertion. We want to allow assertions. And then down here, I think this is the OK. And just press that. I can't see it because it's getting cut off. But yeah, so that will enable assertions now so that we can actually use these. And right down here, if we do get an IO exception, which we will call E, then we'll say e.print stack trace, and then we'll say assert false, and we'll say error could not open file for shader, and then we'll pass in the file path. So that way they just get a nice little error too when that does happen, and plus there. And it says we are never throwing a IO exception. So let's get to that point. How do we open up that file and do all that? So opening up the file is actually the easiest part. We'll just say string source equals a new string, and then you can do files.readAllBytes paths.get file path. And in Java, there's a million different ways to open files. I don't know if any of them are optimum. We don't have to worry too much about whether this is optimized or not because shaders are typically a loading phase type thing, so it's okay if it's a little bit slow. Didn't prove any errors when I was loading things. There's no lag time or anything from this. So this is perfectly fine. And this was just the easiest way I could find to get the string source directly into our string from the file. So simplest way doing this. Next, what we're going to do is we're going to split the string. So we'll say string split string equals, and remember, we want to split on that complicated regex. So what we do is we type in the parentheses for hashtag type. And then we want to say we want to match any spaces, one or more spaces we need. And then we want to match A through Z, capital A through capital Z, and we want one or more of those. And then it will match all that up until the end of the line, which is perfect, which is what we want. So next thing we need to do is if we go to our shader file, what we have is we have this hashtag type vertex. Now what we want to do is we want to find out, okay, where is the end of this line? And the reason we want to find the end of this line is because we need to find out where this to this is so that we can find out exactly what they typed in right here. And then we'll need to do the same thing down here and find out exactly where they typed this so that we can see whether they typed fragment or vertex. I said those backwards, but you get what I'm saying. We basically need to find out, okay, where's the end of hashtag type and where's the end of this line? Then we're going to take whatever word was written there. And to do that, we do a little bit of some jujitsu to get to the end of the line. So we'll say int index equals source.index of hashtag type. And what this does whoops, two parentheses, we just need one, hashtag type. What this does is it finds the first index of where this is. So it'll return 0 in this case, because right now in the file, we're looking from the beginning of the file. Oh, well, the first time this appears is at index 0. So then we want to add in, let's see, 1, 2, 3, 4, 5, 6 to make sure we get past the word. So let's go back into here in our shader, and we're going to say plus 6. And what this represents is the index that is the beginning of that next word, right? So we know that fragment or vertex will come immediately after this index. So then we need to find the end of the line. So we'll say EOL equals source.index of, and we're looking for a /r/n. If you're on Mac or Linux, you'd be looking just for /n. And then we want to look from the beginning, starting from index. So this makes sure we're looking from wherever this one is to the end of the line after where we found this token. And so then it will take us to the end of the line, which, if we go back to our shader, is right at this position. So now if we take the string between these two positions, what do we get? We get that vertex. So let's go back into shader. And what we want to do now is say string first pattern, because we don't know what it is yet. We can't say vertex or fragment. It could be anything. Is source.substring. And we want to go from index to the end of the line. And we want to trim it, which means just take off all the white space and stuff. And this is going to say the result of trim is ignored. No, it's not. There we go. So if you look at this, it just trims, takes off any white space or anything that was attached to that. Next, we're going to do the same thing except for the next one. So next we say index equals source.index of. We want to find another hashtag type, except we want to start from the end of the first line. That way we don't start from the beginning of the file. If we're starting from here, the next hashtag type should be right here. And then that'll give us this index, which we can then use to do the same thing to get whatever this token is. So then we'll go down here. We'll say end of line equals source.index of. We want to do /r/n from our index, because now that's been moved. And also make sure you do +6 here as well. Then we can say string second pattern, so this is like vertex or fragment, equals source.substring from index to end of line dot trim once again. And we can add a comment here, find the first pattern after hash type pattern. And then we will do this and comment down here just so that we know in the future what we're doing here. Find the second type pattern. So then we can say if first pattern dot equals vertex, then we want to say vertex source equals split string 1. And the way that the string will split is we will get some garbage for the 0th index, and then the first index will contain all of this, and the second index will contain all of this inside of that array. So then we can say else if first pattern dot equals fragment, then we want to say fragment source equals split string 1. So whichever they put first is what we're going to put into that split string, and then or into like the fragment or vertex source. Otherwise, we'll just say throw new IO exception. If they typed in gibberish, like maybe there was a misspelling or something, unexpected token plus first pattern plus in, and we'll say plus file path plus, there we go. And so what this will do is it'll go down to our catch block and then throw that error, and it'll basically, actually we could probably just remove this and just leave it as unexpected token, because we already say the file path inside of that catch. So we'll just throw an exception if they misspelled whatever that token was supposed to be. Then down here we will do the same thing. Let's just copy this actually, except for the second pattern, and store that one into the appropriate place. So we'll say second pattern and second pattern, and we do the same exact thing, and we just want to pass second pattern down there and take out that semicolon real quick. Okay, and so now this should successfully store the first and second patterns into our vertex and fragment source. So let's print that out real quick just to make sure we did everything. We'll say print line vertex source system.out.println fragment source, and then let's go into our window scene or our level editor scene, and right up here at the top of init, or just in the constructor is fine too, we'll say shader test shader, equals new shader, and we're going to pass it that file path, which is assets/shaders/default.glsl, I believe. We'll see if that's right. And then import that from our render. Let's run this and we should see it printing out. Okay, expected semicolon right there. Whoops. Let's see. So we get that. And okay, here we go. So if you look, it looks like we did get a vertex and we got our fragment. So that seems to be working perfectly fine. We got that part up. Now let's get the next part, which is compiling the shader. Let's move this into here too, because this is where we eventually want it all to be. So back into our shader, we basically want that compile function. Well, that's actually really easy. If we go into our level editor scene, compile and link shaders. First compile, okay, check for errors, compile, check for, oh, okay, so we just go up to here. Copy all this, and then we want to paste it right into here. And hit OK, and that will import all the things that you need to import. Then right up here, let's just create a few variables, int vertex ID, int and fragment ID. And there we go. And then let's change this from vertex shader source to vertex source. What do we call this? Vertex source. And let's change this from fragment shader source to fragment source. And there we go, that's the compilation. And while we're at it, let's add in the linking to the compilation because those two are very close together. We should probably link and compile at the same time. So let's go down here. You could change the function name to compile and link if you want to be really, you know, a stickler about that, just so that you know exactly what's happening. And then change that shader program ID, copy and paste it everywhere where you see this. And now we have compilation done. Well, that was easy because we already did all the work. And then one more thing we can do is instead of just saying error default.glsl, what we'll do here is we'll say 2 parentheses and we'll put plus file path. That way we get the actual shader we were working with, and then do the same thing down here. And we'll say plus file path. And then I think there's one more, yep, down here. And we'll say plus file path. That way we know exactly which shader there was a problem with. And these assertions will now work since we enabled them. Okay, cool. So that's compilation done. And then we go back into level editor scene. Well, we need a couple more things. Let's copy this comment too and just put it back in there with that shader, just so that we have a little box comment telling us what's happening up there. So compile, and link shaders. That way we know it's doing 2 things. And how do we use the shader? Well, we just say GL use program shader program. So copy that. We will paste that into here. And we'll just say shader program ID. How do we detach? Well, we just say GL use program 0, which we could see in our level editor scene too. Okay, so that's all the functions we needed. Now we can compile shaders, we can link them, and we can use them and detach them. Let's test it, see if it's working all right. We will go into here, and instead of saying like all this stuff, we'll say private shader, default shader. And then right here, we'll say this is the default shader. And then we will say default shader.compile. And then down here, we will say, instead of use program this, we'll say default shader.use. And right here, we'll say default shader.detach. And this should work exactly the same. And we got an error. Okay, so what's this error? It says shader compilation failed. Layout location requires, oh, and that makes sense. So if we go back up to our shader file inside of the constructor, notice how we said this is split string 1 and we copied it. We never changed this to 2, which is the second block of text, which is what we wanted. So if we run this now, there we go. We should get exactly what we were expecting. And it worked just right. And then this is really nice because now if we ever have an error, as you just saw, it will print it out and break out of that thing to let us know. So if we forget a semicolon or something simple like that, it breaks out and it says error in default.glsl. And if we go up here, it says syntax error, unexpected reserved word, blah, blah, blah. And we can be like, oh, we missed a semicolon. Fix that real quick, run it, and now it works fine. And then we can also create new shaders and use them just as easily. So this has been our abstraction of shaders. Didn't really go over how they work still. I'm going to wait for that for a future tutorial when it makes sense, when we're actually be changing some things in them and we need to know exactly what they're doing. So next tutorial, what we're probably going to be doing is possibly talking about starting to abstract this stuff out. This is a large project because this entails a batcher. We're not simply going to abstract out like we did with the shader. It's actually going to be a little bit more of a project, but I think we're at a point where we could start doing it. So next tutorial is probably going to be talking about what a batcher is, how we can use it, and then we will start implementing it in the tutorial after that. And that's about it for this tutorial. We can delete this stuff too. So in the last tutorial, what we did was we finished abstracting our shaders so that we have fully programmable shaders that we can easily create and use several different ones and not have to worry about that creation sort of thing and stuff like that. In this tutorial, what we're going to start talking about is cameras. So cameras are a really important piece of technology in games. What they do is they sort of just define where we're looking at the game world. And in the last series, in the Geometry Dash and the other series, for cameras, we just did a very simple, like, sort of translating everything to make sure it looked right, which we're going to do the same thing here, except it's a little bit different. We're going to use some OpenGL's built-in things, and then we're going to use a couple different techniques that GL gives us. And in cameras, you have orthographic projections and you have perspective projections. And so we're going to talk about what those are and how you can use both of them. We're going to be using orthographic since our game is 2D, but we will talk about all the different things that go into it to make sure that the camera works correctly. And hopefully we'll have a working camera by the end of it. There may be some things that we still need to talk about with shaders that may not allow this. So we'll see where we get to. Before we start coding these cameras and these matrices and all this stuff that we're going to have to talk about, I want to explain it by drawing it out because this is always helpful to me whenever I start a coding project. So, like I said, there are two types of projections. You have your perspective, which is this guy, and you have your orthographic, which is this guy. And the difference between these two is, as you can see, perspective retains perspective. So as objects get farther away from the camera, they seem to get smaller, whereas in orthographic projections, no matter the distance from the camera, the objects remain the same size. Now, when we are declaring these types of, we're going to call them matrices because that's what we're using. They have the perspective matrix, or you can have an orthographic matrix. And when we're defining these, we need to have something called a near and a far clipping plane. And so this would be the far clipping plane, not the near. And then you would have something over here called the near clipping plane. And that would look something like this. And so basically what these are is this defines, and then for orthographic you would have it similarly. This would be the near and this would be the far. These define, okay, these are the objects that I want to retain. So if you have any objects that are in this space right here, we want to show them on the camera. But if it gets too close, we clip it, and if it gets too far, we clip it. Which is why if you get too close to some objects in video games, you'll notice that they disappear. It's because they've passed this near clipping plane. And then we do the same thing in orthographic projection. Anything in this space is visible to the camera. Anything outside of it is not visible to the camera. Now, these are all things that we will have to define, but how exactly does it actually calculate these things? What exactly does it do? Well, in mathematics, we have these things called matrices, which are just big blocks which contain some numbers, x, y, z, w, and then they contain more than those. So they have rows and columns, and if you've ever worked with games, then you may have used something like this. It's just a 2D array is basically what it is. But what's special about these is they have special mathematical operations that we can do. So when we multiply two matrices, they go in a certain order. If we have something like this, they will multiply by adding and subtracting and multiplying certain rows and columns together. So this row would be multiplied and added to this column. What this allows us to do is define certain matrices which we can use in mathematics to transform our objects with one operation instead of several operations. And the GPU is very good at doing these matrix operations. They have optimized them so much to be able to do these as fast as possible. It's something called SIMD, which helps a lot in this area, which is why we use them. What we can do is we can define a couple matrices, and this is called the look at, which is also known as the view matrix. This is where is our camera looking from, and this contains the right vector, and then it contains the up vector here, and it contains the down vector, and then it contains one more vector down here, which is used just to make sure it retains a 4x4 matrix. This is used for depth, I believe. It's used for something. Then you can multiply that by a position vector. And what this gives you is something called a view matrix, which then you can multiply by your clipping matrix, your projection matrix, which then gives you another matrix which we can use to transform our objects from world space to local space. So you take these two matrices and then you would multiply those one more time by the the actual coordinates we're passing in. So if you remember, we passed in a pose to our shaders. And so you would multiply projection times look at times a pose. And what this does is it transforms these, which are preferably in world coordinates now. So these are in world coordinates, and then it transforms them going through this into normalized device coordinates, because the problem is we can't define everything in normalized device coordinates. It just doesn't make sense in our code, and it'll start to look really funny. So we'd rather have a system where we can say, okay, I have an object at like 10, 20. But if we did that in normalized device coordinates, that's huge. That's way too big, way bigger than our object. So we need a way to transform this so that this actually maps out to something like 0.1 to 0.2. Which then is in normalized device coordinates, and we can work with that. We can project that onto the screen and stuff. And so we use this whole thing to sort of transform these world coordinates to these normalized device coordinates in a way that makes sense. And so like I said, I sort of threw this look at matrix at you, this view matrix. And basically all this is this contains the vectors for the camera. So this would be like where the camera is in the world. If you remember in our Geometry Dash series, what we did was we sort of moved the camera, or we move the world in relation to the camera. So if the camera's here and you have an object here, what you would do is you would actually move the object so that it's in front of the camera now. If the camera is in the same space as this object. And so this is sort of what this thing is doing, and then it uses this right, up, and down vector to determine which direction it's facing, because the camera could be facing in any one of the directions in the 3 dimensions, because we are now working in 3 dimensions, but we will define it so that's only looking at the forward Z plane, which gives us the X and Y plane to work with. And then you have this projection matrix, which maps it. So say you want a 1920 by 1080 screen, right? So you want to be able to work with 1920 by 1080 pixels. That's what you want. But then the user's device is actually 4K, so it's like 3200 something pixels by 21 something pixels, right? How do you get from here to here? Well, first of all, it's probably get stretched, which is fine in our case since it's a pixelated game anyways. But you need to scale it, right? You need to say, okay, well, everything I want to here, I sort of need to make it a little bit bigger this way and make it a little bit bigger this way, and then sort of move everything around. And that's a lot of work to do manually. And so what we can do is we can use this projection matrix by saying, hey, no matter what the user screen is, I want a 1920 by 1080 world space to work with. And then this projection matrix is like, okay. And then it converts it to the NDC coordinates, the normalized device coordinates. And then that is able to map it directly to the user's device exactly. So it sort of takes it so that we can define everything as if it were in this space. And then no matter what size the window actually is, it will properly resize it to the size we want it to be. So this is sort of our way of saying, this is how big I want my world to be. You give me that space and I will make sure everything falls within this size of a world. To reiterate, I know this is a lot of stuff, but this is, well, you need to sort of understand this. You have your view matrix, or the look at matrix, which I defined before. You have your projection matrix, which is what defines whether you're in orthographic or perspective mode. And then you have your A-pose, which is the position of all of our objects on the screen. And so what we do is we multiply all these together. I actually have this in the wrong order. You multiply these like this in the shader. And what it does is it multiplies this by this by this. And what that does is it transforms from our world coordinates to our normalized device coordinates. That's what we're doing. And projection tells us how big we want the screen space to be. View tells us where our camera is in relation to our world. So with all that in mind, let's try and code this, and hopefully we can get a good grasp on how all this stuff actually works. All right, so now that we're finally in the code, remember we had this square, and now we want to define this in world coordinates and transform it to localized device coordinates or normalized device coordinates. So what we're going to do is we're going to create a camera class that will contain all the information necessary to do that. So let's create that camera class, and I'm going to add this to Git. Now, like I said, we're going to need a few different things in order for this to work. We're going to need a matrix for F, so a 4x4 matrix, which will be our projection matrix, and our view matrix, which will define how the camera is looking and what type of projection it is. We will also need a private vector 2F. This is the camera's position, right? We need to know where it is in the world. So when we create the camera, ideally what I'm going to give it is just a vector 2F. And this is your position in the world, and then we'll just take that and use it exactly. So we'll just say this position equals the position they passed in, and then we'll initialize those matrices so that they are zeroed out. That way we don't get any errors when we start to write to them. So we'll say equals a new matrix 4F. This dot view matrix equals a new matrix 4F, and that should do everything we need to do. Now, we need a couple things. We need to figure out how to calculate the projection matrix and the view matrix, which I talked about. We need those things. You know, how far do we want it to be? How far do we want it to look out to and stuff like that? And do we want it to be perspective or orthographic? So we'll do all that. The perspective and orthographic we will do inside a function I'm going to call adjust perspective. And I guess that could be misleading because technically we could be in orthographic. And so this would be adjusting an orthographic. So we should call this adjust projection. And what this is going to do is if the window size has changed and we want to adjust the projection, we can do that here. So first what we're going to have to do is say projection matrix.identity. So the functions that we're going to use actually operate directly on this. So this will change as a result of just calling this function, which means you have to be very careful when you're doing stuff using this because if you multiply stuff and everything, it's actually going to change this. You have to be careful because you can get so many bugs by messing that up on accident. But what this does is this initially just gives us a identity matrix, which is a special matrix in math. That means it's like 1. If you multiply anything by 1, you get 1. That's what this is. If you multiply anything by this, you get itself. So special, we need it to actually do our orthographic projection. Then OpenGL gives us this nice function called ortho, or actually, I guess this is JOML since this is the math library we're using up here. And we can use this ortho to define these different things. See, it says we want a left, a right, a bottom, a top. So I want our screen size to be 0 on the left. We want it to be 40 grid tiles that are 32 by 32 each, right? And then I also want it to be 0 on the bottom. I want it to be 21 grid tiles that are 32 by 32 pixels up. Then what we're going to say is the near plane is 0 and the far plane is 100, just to give us a far enough place. So this is basically saying, okay, what we're going to do is we're saying I want the left side of the screen to be 0 and the right side of the screen to be whatever this is. And same with the bottom and the top. And then we can view any objects up to 0 and we can view any objects up to 100 away, 100 units. I'm not even going to say pixels because this isn't really pixels. This is our own units now. Okay, and then that should be it. We now have a projection matrix that has been orthogonified. I don't know, that's a fake word. Okay, let's continue, and we need that view matrix. Remember, I told you that there was also another thing called a view matrix that is important. So we will say get view matrix, and this defines where the camera is in world space. We have to do a little bit more ourselves for this one, but we can still do it pretty easily. So what we have to do is we have to define the camera front. Where is the camera front? Where is the front of the camera? And what I'm going to say is it's a new vector 3f, 0.0f, 0.0f, minus 1.0f. What this is saying is the camera is looking at -1 in the z direction. That's the direction it's looking. It's looking -1. Or the front I should say, because the direction could be anything. But this next bit will let us know exactly where it is. So we say camera up. This is what direction is up. And we'll say 0.0f, 1.0f, 0.0f. We're saying, okay, and then the y direction, the y-axis is the up direction. That way, we know the camera is looking -1 in the z direction, and that is the direction it's looking. There's no ambiguity about that. So then we can say this .view matrix.identity. Once again, we want to make sure that we have an zeroed out, basically, matrix. It's not really 0, but we want to make sure it looks like that. And then we'll say this .view matrix equals viewMatrix.lookAt. And then we're going to do a new vector3f. And this one's going to be a little bit of a long one. So basically, actually, let's look at this real quick. So what parameters is it taken? It takes in something called the eye, the center, up, and you can give it other things too. But those are the things we're focusing, the eye, the center, and up. And so what is that? That's like, where is your camera located at? So we'll say it's located at position.x, position.y, and I'm going to give it 20 in the z direction. So we're saying our camera is located here. And then what we want to say is, okay, where's the center? Where's the camera looking towards? So then we're going to say, okay, well, the camera is looking towards the camera front dot add position.x, position.y, and then 0.0f. And then the last thing it asks for is which direction is up. And for that one, we just give it the camera up that we defined. So we just say camera up. So what this does is it creates a view matrix for us using, okay, this is where the camera is in our world space at this position. We give it 20, that way, since it's looking in the negative z direction, we will have some room to work with up to 20 different z coordinates. And then we say, okay, and where is the center of this? Well, we say, well, it's the camera front. So this is basically saying what direction is it looking at. And when we say camera front to add the position, what this does is it moves the center to just slightly in front of the camera. So if that's the camera, this is the camera front right here. And so now we know, okay, so the camera's looking in this direction is basically what we're telling OpenGL there. And then it can create this view matrix based on all that. And then we're going to return the view matrix since that was what was asked for there. And actually, I think we can just do this because I think this does modify it as well. Yeah, I think that should be fine. If it's not, then we'll get a bug and we'll definitely know that it's not fine. But this modifies the view matrix, this function. So we should be good. But basically, this determines where the camera is and where it's looking at. So we sort of get that all in one. Let's make one more function too. So we'll just say matrix for f get projection matrix, and we'll just return this dot projection matrix. So that one's nice and simple. So now that we have all this stuff, how do we get it to draw using this stuff, right? How do we actually do that? And we have to use something called a uniform variable, which is basically a variable we upload to our shader. So I'm going to go into, whoops, yeah, actually we're going to have to go into the shader too. I'm going to have a whole video dedicated to what uniforms are, but just so that we can get something working so that you guys can see how this works, I'm going to go really quickly through this. So let's go up to default.glsl, and what you're going to do is inside the fragment shader, you're going to go and say uniform mat4 projection. We're going to call this uproj matrix, and then uniform mat4 u view matrix. Actually, we'll just call this u view, and this one will be u projection. And this basically just means, okay, we're going to upload two variables. Once again, I will go over this a little bit more depth in the next tutorial. And then we're going to need a way to actually upload these. So we need to go into our shader and create a couple functions that will help us to upload these to the shader. So what we're going to do is we're going to say public void upload mat4f, and we're going to say string var name and matrix for f mat4, and I need a space there. And so this is going to upload that variable, the variable matrix 4 to our shader with the variable name. So we have to do this thing called int var location equals GL get uniform location. We pass it the shader program that we're using, which is the shader program ID. And then we pass it the var name, which is the variable that we are looking for. And then we basically want to say float buffer mat buffer equals buffer utils dot create float buffer. And then we give it the capacity of our matrix that we were trying to upload, which is just 16 since it's a 4x4 matrix. And then we say mat4.get mat buffer. And what this does is this basically just puts our matrix into this buffer because you need to upload a buffer to GL. That's the only way it works. And then we say GL uniform matrix for FV, and we give it the var location. We say false for transpose because it's not transpose, and we say mat buffer. It's okay if this is all super confusing because I'm going to go over this in way more detail in the next video probably. But we just want to get something onto the screen so that we can see that this is working. Now let's go into our scene, which I think is the level editor scene. And what we're going to do is right before we bind everything, we're going to say default shader.upload mat4f, and then we're going to need a camera. So we'll just say camera for now, like we have one. .get, actually the var name. So we're going to say u projection, and then we're going to say camera.get projection matrix, and then we're going to say default shader.upload mat4f u view, and then we're going to say camera.get view matrix. And this will upload those two variables for us. And then, of course, our last variable, the apose, is getting uploaded with this GL enable vertex attribute pointer. So this basically gives us that. Okay, now let's get an actual camera into our scene real quick, which is relatively simple. We'll just say public camera. Actually, let's make this protected. So that's just passed on to our class, our scene, protected. And then inside of scene, whenever we create a new scene, we'll leave it up to the scene to define the camera. So we'll just do it inside here. We'll say inside init, this.camera equals a new camera. And then we're going to pass it a new vector 2f. This will initialize it to 0 if we just pass nothing in. So it's just camera at 0, 0. We're not doing anything fancy. And we should be uploading the projection and the view. So if we run it, we should see nothing. But we see something. And that's because we're not actually using these. Okay, so let's go into the shader real quick and actually use these. Like I said, you want to do u projection times u view times the vec4. So if we're actually using these, there we go. Now we see nothing. Why do we see nothing? Well, it's because now we're defining this to be like, I think, like close to 1920 pixels, close to 1080 pixels, or units is how big we're defining it to be. And if we go into our level editor scene, how big is that square? It's 1 unit. It's super tiny. So yeah, we need to make this way bigger. So let's just very quickly, we'll make these all in units of 50 so that this is a unit of 100 by 100 instead of 1 by 1. And why are we seeing nothing? Well, I forgot to do the most important part, which is this whole adjust projection thing. So when we create the camera, we should actually adjust the projection so that we have the projection we wanted, right? We were not really creating a projection matrix, so it was sort of messing everything up. And I also went into the level editor scene and changed these so that they went from 100 and 0 instead of minus 50 to 50. And now when we do it, we get a square that is much different, and it's down in the lower left corner of our screen now. And then what we can do, just to make sure that this is all working exactly as it should, is if we move the camera to the left in here, we'll say camera.position.x minus equals dt times, and then we'll say like 50.0f. And then let's make position a public variable just so that we can do this and see if it works. And we should see the square move to the right, which it's doing. So we have a working camera now. And I talked about those uniforms. It didn't really go over them. I promise we will go over those in way greater depth in the next tutorial, which we will talk exclusively about shaders and uniforms and everything about shaders, how they work and how the programming language works, just so that you guys know what's going on there. But I hope the camera part made sense. I hope it makes sense what the view matrix does. It defines how the camera is looking. What the projection matrix does, it defines how many units we want our world space to be. And then how we use that in our shader to adjust from world coordinates, which we get in here, to normalized device coordinates, which we get out right here. This has been a little bit of a long one, but there was a lot of material to cover, and I really wanted to get it so that you guys really understood what was going on. If anything doesn't make sense, please leave a comment, and I would love to go over it in more detail if you guys need that. So in the last tutorial, what we did was we covered game cameras and how you can use transforms, specifically view matrices and projection matrices to create, move the world around the camera basically, sort of like what we did in our previous series. In this tutorial, we're going over shaders, and we are going to be going over how to upload shaders to the GPU and then talk a little bit more in depth about how the shader programming language works, the different sort of keywords that you should look for and what they mean, and what you can do with them. So we'll be doing something cool, which should be showing right now, hopefully, and that will just sort of show off what you can do with shaders. They are really cool pieces of technology that can be used for literally anything you can think of, and we will take a look at them today just to see what we can do with them. So let's figure out how they work and get that done. So I figure the best way to try and understand shaders is to use a drawing and a little bit of diagramming. So I have right here a little shader program that doesn't really do anything. This would be the vertex shader, and you can tell that because it has these layout things, which will explain what all this is. So remember we talked about how graphics programming works, and we said we have these things called VAOs, vertex array objects. And what this contains is a bunch of attribute pointers, right? And we define these attribute pointers inside of our big vertex list, which means like, oh, we want attribute 0 to be x, y, z for our position. We want attribute 1 to be u0, u1 for our texture coordinates, so on, so forth. And so we sort of define the way these things work using GL vertex attribute pointer. And we say, okay, we want 0 to contain these three, and then we want attribute pointer 1 to contain these, and then a color for attribute 2, so on, so forth. And then what happens is we create that inside of this VAO. Then how do we access all this data that we have buffered to the GPU? Well, we access them through these things called layouts. And so inside of our shader program, the vertex shader, we have this layout parenthesis location equals number parenthesis, and this corresponds directly to our attribute pointer. So you'll notice I've color coded these. The green is attribute pointer 0, the red is attribute pointer 1, the blue is attribute pointer 2. And then these could be any type that you want. So you just have to make sure that they match the types in here. So in this case, I have a vec3 for location 0, a float for location 1, and a vec2 for location 2, which means we could not have this u2. It would just have to be one variable. And then for the last one, we would have to have a vector 2. So we'd have to have two floats inside of there. And so the way that the GPU knows this is because we've already specified how it can find everything, and then it basically just uses these numbers to sort of index into the array, the data that we've given it, and it's like, okay, I know that the float's going to be in this position in the array, and then it can go and find it for us, and then we can just access it directly inside of our shader program right here. Now, there's this other thing though. What if you have variables that apply to several vertex attribute objects? Vertex array objects. Things like cameras, right? Because the view matrix and stuff, I spelled that wrong. The view matrix and stuff, that applies to every object in your scene, right? The camera position doesn't change from object to object. So typically, you would want one shader, and you would only have to want to tell the GPU, hey, we're using this, just keep it there, because we're probably going to be using it for a few different things. Then what happens is we can upload it. Okay, so we upload it using these things called uniforms. And so uniforms are these things that stick around, right? So they stick around from object to object and don't have to be respecified. So every time you bind a new VAO, these things all change, but these things only change once you upload a new uniform. And how do you upload a variable to the GPU? Well, the GPU uses IDs, just like we did for all of this stuff here. And so basically what you end up having to do is you have to say, okay, first I need to find the variable's location in the GPU. So you say something like variable location equals, and then you get some function from GL, and you pass it the name of the variable you're looking for. So say we were looking for U color. It would say, okay, I'm looking for U color, and then it gives you the variable location, puts it in here. Then next thing you have to do is you use another GL function, which is like GL uniform, and then the type. So U color is a float, so you would say F4 or something like that. We'll look at it in more detail. I can't remember these. There's so many. But basically you would say that, and then you would say, okay, I'm giving it to this shader. So you would give it the shader's ID. And then you would say, and I am looking for this variable. So you would give it the location. And then you would say, and I'm uploading this value. And then you would give it the value. So that's basically all there is to it. And then what the GPU does is it uses the ID that it has obtained through this. It uses this ID saying, okay, so this is a shader we're looking for. Actually, you would use the shader ID in here. Let's backtrack a little bit. So basically you would say, I'm looking for U color, and you have to specify the shader you're looking for it in. So then you would pass in your shader ID here, which if you think about it, that makes sense, because why would you look for this U color if you were looking in a shader that didn't even have something called uColor. So you tell it the shader ID, which is our program that we're looking in, and then you tell it the variable name. Then you do this GL uniform. I think it's like 4F or something, not F4. But you do this, and then you say the variable location and value. And you do have to make sure that in between these two calls, at some point you have said shader.use. So you have to make sure you're using the shader, because this call expects to upload it to the current shader being used. And so if you just pass this in and pass this in, and you don't have some shader being used right here, then it's just get passed into whatever shader was last used, and that variable location might not even exist, and then you could get an error and you have no idea. So between these two, just make sure you call shader.use if it's not already being used, and then you can upload it just using that location. So it's pretty straightforward. It's really hard to grasp when you're first learning this stuff. It was for me. And I really want you guys to understand how all these things are connecting together, because it's not that hard, but if you've never done this stuff before, it can be difficult. And so just really want to hammer home the point. We have these VAOs, which we defined. We defined what these attributes are. We defined them in an array that looks like this. And we said, we want this array to be formatted this way. And then we specified all that format in our code. Then what happens is inside of our vertex shader, we can say, okay, we're getting this location here, we're getting location 1 and location 2, which is going to match up with our VAO, and so then the types would match with whatever types we passed in down here. Then we have these last things called uniforms, which are basically variables that we can upload to shaders, and we just look for the variable's location. First we ask for where it is in the shader, then we just upload it to that shader using GL's function, and then we pass it the value. And then the last part of a shader program is the main program, or the main function. The main function is in charge of, it's like the entry point for the program, just like all programming languages have. And basically you just write all your code inside here. And then you end up, for GLSL, you say GL position equals, and then you put some vec4 here. And what that does is that ends up outputting the final position as whatever this vec4 is for this vertex. And then I feel like one last thing that would be nice to know about shaders. So we have these in and these out specifiers. So in means something that you're taking in. So we're expecting these variables to come in through here. Out, you could specify something like out vec3 fpose. And that basically just means you're going to declare some variable inside your main function called fpose. And inside of your fragment shader over here, you're going to have something that looks like this in vec3 with the same exact name, fpose. So for every out you have inside of your vertex, you must have an in inside your fragment shader, because these two are directly correlated. And this guy is going to expect to pass all his outs to this guy's ins. And then this guy has one out, which is the color. So you would just say out vec4 color. And then this color is what gets output to the next stage in our programming pipeline, or our graphics pipeline, and then it continues to go through. Like I mentioned in the graphics programming, this operates on vertex. So this guy is on the vertices of an object, so these would be the vertices. Fragment shader operates on the interpolated data sent in from this. So if this guy passes in position to here, then what this guy gets is an interpolated position between the two vertices, well actually all vertices of wherever it is within the object. So it would get, if it was here, then it would get this interpolated position, it would get this position, and it gets it all at the same time. So we don't have to specify any of that, it interpolates by itself. It's called a fragment that it's operating on, and this is called the vertex that it's operating on. So hopefully that clears up some things. Let's code this part, and then we'll actually code a shader to do something cool, and we will sort of see how all this fits together. All right, so picking up where we left off, we had that nice camera movement that we were doing inside of the level editor scene. We were just moving this around. And then we did this thing, the upload map4 function. We're going to create a bunch more of these just so that we have all the functions we might need, so we can upload any type of variable. Because for every type of variable you want to upload, you need to create an upload function. And if you want to know like the different types and stuff, just look up the GLSL documentation, and then you can just go into here. And so basically this will just tell you all the different documentation and stuff. This is for GLSL4, which should be fine. And then you see you can just go into here. It's got a bunch of built-in functions, tells you all these different things. And then if you want to, Chronos.org is another good source for this stuff. And then this just sort of lists like the different types that you can have in GLSL, which is helpful. Now back to this. So let's go. We want to go into our shader class, which we created inside of our render. And we created this function sort of on the fly. You should understand it a bit more now. What we're doing here is we're saying, okay, get the location of the variable for our shader program. And then what we're saying here is the map buffer. So matrices are the only kind of weird things because we have to sort of flatten them out so that they are actually in a 1D array like this. And this would actually be 16 wide. So what we do is we create a buffer of 16 variables wide, and then what we then just sort of stuff all of our stuff into that buffer using this function. And then what we do then is we say GL uniform matrix 4FE, which is expecting just a 16 long array, and then we give it the location. We say whether we want it to make it a transpose or not, which is a linear algebraic function. We do not, and then we just give it the buffer. So it's the only one that's kind of weird. Everything else should be relatively straightforward. Let's do one more thing inside of our use. So let's go up to the very top, and then we are going to create a private Boolean being used, and this is going to initially be false. And so what we're going to do is we're going to go into our use program. We'll say if not being used, and then we want to use it. Otherwise, we don't need to do anything because it's not being used. And then inside of detach, we will say being used equals false. Also, being used equals true once we start to use it. And this will just be nice because then we can't accidentally use the shader twice. If it's already being used, we don't waste GPU time rebinding a program that's already bound to the GPU. It probably optimizes that away, but I wouldn't count on that 100% sure, so we'll just do this. Then what we can do is inside here, before we do this thing, like I said, we want to make sure we're using the shader. We'll just call it use to make sure we are absolutely using the shader every single time, because you don't want to call this and then not be using the shader that you're trying to use. Then what we're going to do is we're going to create the upload vec for f. We'll try this one. And so we're going to take in a variable name, which is the name of the uniform we're looking for, and we'll take in a vector for f, and we'll just call this vec for f. And then we're going to follow this same exact pattern. We'll say the variable location equals GL get uniform location, shader program ID, and the variable name. So the shader we're using, and then the variable name we're looking for, we'll say use to make sure we're using it, and then we'll say GL uniform matrix, GL uniform 4FV. So for float vector is what that stands for. And then it expects, if you look at this, a location, which is our var location, and then a float buffer or a float array, which is the value, and we could say vec for f dot. And then I did this really simply. Let's actually just change this to vec2, or just vec, because it'll make it a little bit easier. You can literally just say vec.y, vec.x, vec.y, z, and then w, and that should upload it. And don't do the v. 4f, just 4f. Sorry about that. Okay, so that's for vectors. For vec3, you would just change this to a 3, you would change this to a 3, and so on. We'll do another one, public void upload float string, not that string, string var name, and float value. And we'll say int var location equals GL get uniform location. And we will pass in our shader program ID, and we'll pass in the var name. Same thing again, use it. And then we'll say GL uniform 1F, and location is going to be our var location. The float is going to be our value. Okay, you can also do ints and mat3f, and there's another one for texture that we will get to eventually. I'm going to show one of the ints because, well, actually, we're just going to use int. So upload int string var name float, or actually this is going to be an integer value. I'm literally just going to copy this now because it gets very repetitive. These are the only repetitive things that we really have to do too. And we want to do 1i since we're doing an integer. So that should be good. Okay, now I'm going to do the same thing for vec3 and vec2 and matrix 3 and matrix 2. I don't think we do have a matrix 2 actually. Yeah, so just matrix 3. So I'm going to time lapse this real quick because I'm literally just going to be copying and pasting stuff and changing a few different things. All right, so I finished that up real quick. One thing to note, just make sure when you're doing the matrix 3, capacity is 9 for the float buffer, and make sure it changes to 3FV. Don't forget that part. But yeah, so I just sort of created all these, and we should be able to use them now. So let's actually use them and create a shader real quick. If we go back to our level editor scene, you can see we're already uploading 2 uniforms. So we have U projection and U view. Let's upload a third one, and we'll call this one U time. So we'll say upload float U time, and we're going to call this time.getTime. So we're literally just going to pass the time to it, because then we can do some time-based animations in our shader, which is kind of cool. And then let's go into default.glsl. Since we pass in time, we now need to accept time. And cool thing about uniforms, you can have it inside of your vertex or inside your fragment. I'm going to do this one inside the fragment because I think it makes a little bit more sense. So I'm going to go uniform, float, and utime. Have to make sure it's the same exact name. Then what we're going to do is we're just going to say color equals sign of utime times the F color. So just going to take the sign of it, which means it should sort of blink on and off the colors. And let's see if that works. And sure enough, it's blinking on and off. But that's not the cool thing we're going to do. We're going to do something even cooler than this, because this isn't that interesting. Let's get real here. So I'm going to think of something real quick, come up with a program, and then we're going to implement it. Okay, so we'll do a couple things here just to sort of illustrate the power of shaders. And this still doesn't even like really touch what they can do. So first, what we're going to do is we're going to convert our image to black and white, which is pretty simple. So black and white just means it's the average of all the color. So we'll say f.color.x, or actually we can say r, fcolor.g, and f, this shouldn't be commas, this should be plus, fcolor.g plus fcolor.b over 3. So we get the average, and then instead of, oh, that should not be there, that noise, that's what we're going to do in a minute. So instead of just doing fcolor, we'll do average, vec for average, average, and then we'll do 1 for that last one. Then when we output this, we should see black and white, which we get a black and white image now. So it's the same image, it's just been converted to black and white, which is pretty cool. And you can do this with anything. And as you saw, it's 2 lines, just 2 lines to do that. And then it automatically converts everything. So that's one cool thing. Another cool thing, I found this little thing on the internet, and it basically is a noise calculating function, which I think it would be really cool to go in depth into noise specifically. We will not be doing that in this tutorial, but maybe in the future we'll have something that covers all the different, like some different types of noise and everything you can do with that. But what we're going to do is we're going to say fcolor times noise, and this is just some random number generator between 0 and 1 basically is what this does, based on a 2-dimensional input, which is our thing. And so these are like sort of seeds that you would have, and then this is just like a modulus almost. So the sign basically clamps it between a certain amount, and then the fraction gets that out of there. So there's a lot in this little one line, but it generates this cool thing that we see here. And you see it's this really cool noise thing that's just going according to the position. And why is it changing as the position moves? Yeah, and honestly, I'm not actually really sure why it's changing as it moves, but it's cool. So a cool noise function. Like I said, in the future, we might go in depth more about this. This is where I got that from too. They have another thing called Perlin noise. You should try and implement it yourself if you really want to, because Perlin noise is used for a lot of different things too. And then if you use Perlin noise with time, you can create some cool looking things like clouds and stuff. So just some cool stuff that you can do with this. But I hope this covers up shaders a little bit more. There are some things that we still didn't really get to very specifically, like how you would create functions and stuff. It's a whole programming language, so it's a lot of stuff. We're going to be using it for like the bare minimum just to get our textures and everything, but shaders are super powerful and you can use them for literally anything. I think some game companies even use like geometry shaders to manipulate hair using physics and stuff. And then they run their physics calculations inside of shaders and everything too. It's insane using the GPU to do a lot of stuff. So hopefully in the future we'll get to go over a lot more stuff that we can do with this, because they are so cool and I really want to learn how to use them better too. In the last episode, what we did was we talked about shaders in more depth, and I tried to give you guys a better explanation of what they are and how you can use them to your advantage. We will be using them just a little bit more in this episode when we start using textures. So we're going to go over what textures are, how you can use them, and all the components that goes into loading a texture into OpenGL, and then finally displaying that texture on an object. So let's see how textures work, and then we will code it and see if we can get it working. Textures are just images. That's literally all they are. It's very simple, but there's a few things you have to worry about, because when you start applying textures to objects, there are things that can happen. Say you have this texture right here, and it has width W and height H, and you have this quad right here with the vertices V0, 1, 2, and 3, and the two triangles, the blue and the red triangle, labeled here. Now, let's say you want to plaster this image to this quad. Well, you would do something called texturing it. And the way you would do that, you would basically specify where you want these things called UV coordinates to be, how you want it to map. And all that means is basically the picture has these coordinates. So the bottom left is 0, 0. Bottom right is 1, 0. The top right is 1, 1. And the top left is 0, 1. And as you can see, those are just the XY coordinates mapped from 0 to 1. Now, what you can do is you can then use these UV coordinates on the picture and map where you want each of these coordinates of the picture to go to on the quad. So then in this case, you would say, okay, I want vertice 2 to contain 0, 0. Vertice 3, I want to contain 1, 0. Vertice 1, I want to contain 1, 1. And vertice 0, 0, 1. Then what it does is it maps each of these to each of the texture coordinates that we have defined over here. And it basically maps the image to fit directly onto this quad. But we have to worry about a couple things, because there are cases where, what if that width and this width do not equal each other? So width 1 does not equal width 2. Well, we have to specify to OpenGL what we want it to do. We have to say, okay, if width 2 is greater than width 1, if we're stretching the image, I want you to blur the pixels. That's one of the options we can say. We can say, I want you to blur the pixels, which basically means it'll get blurry as it gets stretched. You can also say, I want you to pixelate. And what pixelating means is exactly as it sounds. The pixels retain their form and they just get bigger. And there are a couple other things that you can specify as well. So that's the first thing you have to worry about. Second thing you have to worry about is, what if you have two more vertices over here, and then you have a texture coordinate here that says 2, 0, and this texture coordinate says 2, 2. Well, wait a second. Our texture is only specified in terms of 0 to 1 and in terms of 0 to 1 this way. So what happens if we grow outside of the texture coordinates range? Well, that's something else we have to specify to OpenGL. And so we can specify we want it to wrap, which basically means it starts to repeat, and it basically just repeats the image onto the next quad. Or there are a few other parameters that you can find as well. And I will leave links in the description where you can find the documentation for all this stuff so that you can examine exactly what options are available. So when we get a texture, what we have to do is we have to store the texture into an array. And we can use this library called STB, which will handle this for us. And we basically just store it as RGBA, RGBA, and so on, which is each of the pixels just stored in one array. Next, what we have to do is we bind the textures that we are working on, this texture specifically, and then we list out the parameters we want for this texture. So we say, okay, I want you to pixelate or blur, I want you to wrap or not to wrap, or to stretch, all those different things. And then all of that gets sent to the GPU so it knows what it's doing. So we select our parameters as the next option. And then finally, we upload it to the GPU. And when we're uploading, we have to specify the exact format. I know I spelled upload wrong too. We have to specify the exact format it's coming in. We have to say, okay, it's going to be RGBA and it's going to be specified in this order. Some systems are little endian and some are big endian, which just basically means that these could be flipped. So we have to specify, okay, we're sending it into you as an RGBA. And then we have to say, okay, we're sending into, it's this big. So we send in the width and we send in the height so that it knows how much data it has to reserve for this texture. And then we say, okay, and by the way, this is a GL texture 2D. And that last thing is because there are actually different types of textures we can apply, which we may take a look at in a future series. And this one, GL texture 2D, is all we will need. So these are the 3 steps we will have to worry about as we are creating textures. We need to first get the pixel data, then we need to create an ID and assign parameters so that OpenGL knows what kind of image it's uploading. Then we finally upload it to the GPU and it automatically takes on all the parameters and it assigns that texture. Then when we actually want to draw it to an image, what we do is we assign UV coordinates and then we have some sort of uniform variable, which GL gives us a special case that allows us to choose textures that we have uploaded. And so basically we can bind a texture and tell the shader exactly where it is. So we can do something like, it's not this exactly, but we'll say bind and then we give it the text ID. And then we give it a slot. So you have slots 0 through 8. There may be more depending on your GPU, and there may be less depending on your GPU. I think I limited mine to 8 just to try and catch lower end GPUs as well. But basically, you assign it to a slot, and then inside of our shader, we can then get it out of that slot, and we can sample it to apply our texture to our image using the UV coordinates attached to the vertices. So there's quite a few steps. We'll go through it one by one, and let's try and code it so that we actually get our textures applied to the images. I'm back in our level editor scene, and I'm just going to run it so that we can be refreshed with what we did in the last tutorial, which was we got the shader working that basically just applies a noise texture. Well, not a texture, but it applies noise to our image, and that was kind of cool. Let's go back into our shader and just take out that noise for now, though, because it will not be useful for what we were about to do. So run that one more time and you should just get back to our regular square. So back into our level editor scene, the first thing that I want to do is prepare for the textures. And the way we can do that is by specifying a couple more variables in here. So this will be the texture coordinates, and I'm going to change these all so that they are correct. And to get that cool multi-cursor thing, it's pretty simple. Just hold down your scroll wheel and drag, and you will get a multi-cursor. Then up here, I'm going to say this is our UV coordinates, because this is what they are going to be. And the UV coordinates, like I said before, are just what maps it to where our triangle should sample the texture from. And so like we said, bottom right is 0, 1. Top left should be, actually bottom right is 1, 0. Top left should be 0, 1, top right should be 1, 1, and bottom left should be 0, 0. So that should align perfectly with our triangles. So now that we have the UV coordinates, let's specify inside of our vertex attribute pointer that we are now getting another new variable in here. So we'll go up to here and we will say int UV size equals 2. There's 2 UVs. And I found out that we actually don't have to guess about float size in bytes. So you can actually go, Java has this built in. If you just do float.bytes, that will get us the float size in bytes. And so then let's just change this one as well, float.bytes, which is nice because it's always better to use the built-in because it could be different than what you think it might be. Next, we want to enable an attribute pointer for the UV coordinates. So we'll say another vertex attribute pointer. This one is going to be assigned at 2. Its size is going to be the UV size. The type is going to be a GL float. We're just going to leave them as floats because they can range anywhere from 0 to 1. Normalized is false. The stride will be the vertex size in bytes. I think we have that in bytes. Yep. And then the offset will be the position size plus the color size times the bytes, because we need that to be in bytes. And I know this is blocking, so you can't really see. So here we go. Vertex size in bytes, and then the position size plus the color size times bytes to get the correct offset. Then let's go back over to here and let's just add in UV size to our total vertex size. And then finally, we just enable that vertex attribute array. And so once again, this is just adding another column so that it knows we now have 3 vertex attribute pointers, because we have 3 different attributes that we'd like to have in our vertex. These are malleable. You can change them. You can make them whatever you want. I want to really hammer that home because it's something that I did not get for a long time. These are anything you want them to be. Now, let's actually talk about loading in textures. How do we load in the textures and get them into the scene? I'm going to go ahead and just create a whole texture class, because I feel like there's no sense in doing this in here and then abstracting it out, because it is quite straightforward and what we would be doing. I mean, textures will be contained within the texture class. So we'll say public texture, and we're going to take in a file path, which is the path to the texture resource. Then we'll say, let's store a few variables, okay? So we're going to need an ID, and we are going to want to store the file path for debugging purposes. So we'll take in a string for a file path, and we will take an int for the texture ID. Then we can go and we can start to build our texture when it is called. So we'll say this.filePath equals the file path. Then we want to generate the texture. So let's say generate texture on GPU. And we're going to say the text ID equals GLGen textures. And this is a special call. It's like GLGen buffers, except this one actually generates a texture ID for us, because they are stored, I think, probably differently in memory, optimized to be better in this scenario. So then we'll say bind the texture, and we want to bind a GL texture 2D, and the texture we want to bind is the ID we just created. Hit Alt-4 to import these. So we bind the texture, which means we can now set the texture parameters. Those parameters I was talking about, how do we want it to act? First, we're going to say we want it to repeat the image in both directions if somebody specifies a UV coordinate that is greater than the texture's width. So to do that, we say GL text parameter I. So this is just GL's like basic way to set parameters for a texture. And I think the I is for info. So this is a parameter info that we're setting. GL texture 2D is the one we're operating on. We want to say GL texture wrap S GL repeat. And all this says is the texture wrap S is a special form. It's like what they call it when it wraps, or when it goes from 1 to 2, because then it would technically be wrapping from 1 to 0. So they call it wrap S, which is the U or the X, and then T is Y. So it can get a little confusing, but we have to specify it for what to do when it wraps in the left and right direction, X, and then up and down direction, Y. So then we'll say GL texture 2D, and then we'll say GL texture wrap T and GL repeat. And typically you'll want that wrap S and wrap T to be the same type of thing. I don't know many cases when you might want to change that, but it might arise. Now we want to say when you're stretching the image, we want it to pixelate. Since we are doing a pixel game, we don't want it to blur, because we're not going for realism. We are going for our nice pixely Mario character. So we'll say GL texture 2D, another parameter. And this is the GL texture min filter, which basically just means the image is stretching. And we say GL nearest. And what that is the method it uses to sample the pixels. And instead of blurring, it's going to choose the nearest pixel. So it's going to, instead of interpolating and blurring that pixel, it's going to choose the nearest one, which just means it turns into a bigger pixel. That's all that means. Then when we're shrinking an image, we also want to pixelate. So in both cases, we want to make sure we pixelate. And so we'll say GL text parameter I, GL texture 2D. and we'll say GL texture mag filter. So the min filter is for stretching, the mag filter is for shrinking, and we are going to specify GL nearest once again. And I could see why you would want to change these to be two different functions for stretching versus shrinking. So there is a chance you might want to change those. Next, we need to load the image. We need to get that RGB data. So we need these things to store the width, the height, the channels in the image for the library that we're going to be using, which is STB. So we're going to create these int buffers, and they're all going to be of size 1 because this is the only way that, well, it's not the only way, but it's the way that the library we're using works to get all this information. So then we're going to say int buffer height equals buffer utils.create int buffer. That one's also going to be size 1. Int buffer channels equals buffer utils.create int buffer, also going to be size of 1. Then we can actually load the image. So we'll say a byte buffer, our image, and I'm going to import that, and then we're going to say stbi load, which is the library that we're using. Let's import this. STB is an image loading library. It actually does a lot of stuff. We're going to use this for loading our sounds too later on in the series. So what does it expect? We see that first it expects a file name, which says a byte buffer or a char sequence. We can just pass in the string and that will be implicitly converted to whatever we need. Next, you see it says we need that int buffer. That's why we needed to create these as int buffers. And X just means the width, Y means the height. Then channels is just like, is it RGB or is it RGBA? So it'll return 3 if it's RGB and 4 if it's RGBA. And desired channels, if you set that to 0, it'll just make it tell you exactly how many channels are actually in the file and load it as is. That's how you load the image. So now we have the RGB data stuck in this image. Now, we say if image does not equal null, so if the image loaded successfully, then what we're going to do is we're going to say GL text image 2D. We're going to say GL texture 2D. So this is where we're actually uploading the image to the GPU. Then we're going to say we want the level 0. This is something for map levels, which we will talk about in the future, but we don't really need them in this case. And 0 is the maximum level, which is what all of our textures will be at. So specify a 0. It's like the default setting. The format. We're going to say GLRGBA for now. So we're going to assume that all of our stuff is in RGBA. The width is going to be our width.getZero. When we pass in the width to that function, it actually stores the real width inside of it. So we should have the width and the height in there. The border, we're going to specify a 0, which basically means we don't care. GLRGBA is the format. The type is GL unsigned byte. We have a byte buffer. It's an unsigned byte. And then finally the data. So image, which is what we just got right here, this byte buffer. And I'm going to move this to the next line so that you guys can hopefully see that whole thing. So GL text image 2D uploads the pixels to the GPU. So this creates a buffer of size width times height, and then basically just puts all of this image data in there. And we tell it this is exactly the format it's going to be in so that it knows what to look for. Now, if we didn't get the image, we want to say assert false trouble. Well, actually, we'll just say error could not load image, and then we will say plus the file path, just so that we know that we had an error. And we'll say texture, just so that we know that this came from the texture file in the future if this ever happens. This is useful. You want to be able to tell yourself these things in the future if something ever happens, because you need to know what actually went wrong. Last thing we need to do is say stbi free, actually image free, sorry, got that backwards, image free image. What this does is this frees the memory that STB has allocated. So this is allocating memory, not using Java's virtual machine. I think it's interfacing C directly, which means that if we never free that memory, it's a memory leak, which sounds scary, but it's not too bad. You don't want memory leaks happening in your code though, so just make sure to free this, because now that we've uploaded the image to the GPU, we no longer have any need to hold on to the image data. It's already up there. That's all we need to do. All we need is this texture ID so that we know how to get to the texture. Now, we want to be able to bind and unbind our textures. So let's make a public void function called bind. And this will just make one call to GL. So we say GL bind texture, and then we're going to say texture 2D and pass it the text ID, which is exactly how we bound it right up here, right? Then when we want to unbind, we'll say public void unbind. We'll just say GL bind texture, GL texture 2D, 0. And 0 is like that default, just that we bind nothing. So bind, unbind, and creating the texture and uploading it to the GPU. We have all of it done. Now let's see if we can actually bind a texture and upload it to the GPU. Let's try it inside of our level editor scene. So what we'll do is we'll go up here and we'll say private texture test texture. And I'm going to hit Alt and import that. Whoops, I completely imported the wrong thing. Make sure you watch what you're importing. You don't want to import the wrong thing. So this is the texture we want to import. And then inside of here, what we're going to do is we're going to say this dot test texture equals a new texture. And I'm going to get a texture, and it will be attached to the link where the code is. So just go to that. If you want to use my image, you can use whatever image you want though, and it should work the same. So I'm going to say assets / images / test image.png. Just make sure your image has alpha, because if it doesn't, then it could turn out wrong. And my image is actually a JPEG, so I'm just going to change that to JPEG. Next, we want to be able to load this image and actually display it when we are drawing our quad. So that involves just a couple extra steps. So we're going to need a new function in our shader because this is the final function I talked about that we didn't get to. And it's pretty simple. It's basically the exact same thing as upload int, but we're going to call it upload texture, just that we know this is actually for when we want to upload a texture. And I'm going to call this slot instead of val because this is a texture slot. And I'm literally just going to copy this because it is exactly the same as uploading an integer, because that's all we're uploading is the texture ID, the integer of the texture. Now, the thing that's going to change though is inside of our shader, we're not going to give this a type of an integer. What we're going to give it is we're going to say this is a uniform. This is going to be a sampler 2D. And I'm just going to call this text slot. Let's call it text sampler, because that's really what it is. It's a texture sampler, but we didn't give it the integer. We didn't call it an integer. We called it a sampler 2D. So that's why when we created that function in the shader, we gave it a different name, because this is technically a different type, but OpenGL sorts it all out internally and figures out what exactly we mean. Now let's go back to our level editor scene. So then we've created this texture. Now when we go down here, we want to upload the texture to the shader. So we'll go right here and we're going to say upload texture to shader. And what we have to do this is we say default shader.upload texture first, and we're going to call this text sampler because that's the name we just gave it. And the slot is going to be texture slot 0. So this is different from the texture ID. What we're saying is we actually want to upload the texture ID that is at slot 0. So kind of weird, I know, but this is how it works. Then we have to say, okay, GL active texture. We want to activate the texture, and we're going to say GL texture 0, which is GL texture slot 0. And then lastly, we say text texture dot bind. So what happens here? What is happening? We're saying, okay, we're uploading a texture to OpenGL. We're using slot 0. Then we say, okay, now activate slot 0 and put our texture into there. So this activates the slot 0, and when we bind our texture, it pushes it into this slot specifically. And now we have our texture uploaded to our shader. So if we run this, what's going to happen? Nothing. We're going to get an error. So the reason I got the error is because of that thing that I just warned you about, to make sure your image has alpha. Mine does not. So I have to make sure that I don't have RGBA. We'll fix this in a minute too, so that we don't get nasty errors like that. But what I was going to say is if we run this, it still looks the same. And that's because we haven't actually applied the texture in our shader. So, whoops, this isn't our shader. Let's go back to our actual shader. And what we're going to do is we're going to specify, we added a new location in our vertex shader. So location 2 should be a vector 2. And this we're going to call AUV. So the UVs. Then what we're going to do is say out vec2 FUV. So we're going to pass, actually, let's call this text chords because I think that just makes more sense. So A text chords, F text chords. So these are texture coordinates. Then we will say F text chords equals A text chords. So we're just going to pass the texture chords from the vertex to the fragment. Inside here, we're going to say vec2 F text chords. And then inside of here, instead of saying color equals F color, we will say color equals texture. And then we're using our text sampler. And we are using our F text chords. So this will sample whatever color is on the texture at this position, and then it will place it into our color. So then if we run this one more time, you should see we get the image. So I did a portal cube for my image. One thing you might notice is that the image is upside down. Now, one easy way to fix this is just to go back to our level editor scene and scroll all the way up to the texture coordinates and flip the bottom and the right. So we'll make this one, and we'll make this 0, and this one. And so in doing that, we are basically just flipping the texture in the actual image. Because like I said, these are literally just specifying where to sample it and where to place it onto our triangle. Last thing I want to do is let's go back into our texture class so that we don't get this error again. What we can do to fix this is we can say if channels.getZero equals 3, that means it's an RGB picture. It just has 3 channels. We will do this. Otherwise, if channels.getZero equals 4, it's an RGBA picture. So we can change this. We'll copy and paste that to RGBA. And then otherwise, if it's none of those, then we don't know how to handle this. We will say assert false error in our texture, unknown number of channels, and we will say plus channels.getZero. So this should fix it so that we no longer get errors if we upload an RGB or an RGBA picture. And that's it. I kind of went through some of this stuff a little bit fast, so if anything doesn't make sense at all, please leave a comment and I will respond to that and try and clear things up with you guys. But yeah, this is texture loading, and now we can load images into our game, and we will continue to expand upon this in the next tutorial. In the last tutorial, what we did was we did texture loading, so now we can load textures into our game. And now it's time to start getting into some higher level engine stuff. So we have some of the low level stuff done. We can display graphics. So the next logical step is to bring it up a level and start doing some of the abstraction layers that we will need to make it simpler to code in our game engine. So I will be talking about entity component system. And this will hopefully be better than the last tutorial that I did on this, because I will actually be discussing the different types. I didn't know much about it last time I recorded the tutorial, but I've researched it a bit. We're going to be doing most of the same stuff that I did in the last one, but I will explain how you can do it differently if you would really like to. So let's see what entity component system is and the different types of things that you can do to code it. In order to understand where we are now in terms of the entity component system, we sort of have to go back in time to the beginning, when we first started doing game programming and programming in general. So in the 90s, OOP, object-oriented programming, was huge, and it was considered the de facto standard for creating good programs. And so people would create these large hierarchies that went very deep and started with something like an object. And then so in terms of a game, we would have like an object, and well, we could have a UI or we could have game object. Well, game object could be a player or it could be an enemy. Well, an enemy could be a certain type of blah blah. UI, we could have a text or a button. Well, we have several different buttons. We have several different types of text, and so on and so forth. This gets very large, very complicated, and does not end up helping 90 or 100% of the time. It's just not good. So we sort of moved on from this approach. I'm guessing that probably in the early 2000s, they started coming up with this component pattern. So once the hardware started catching up and we were able to do things faster and easier, we decided to start doing it in a different way. And so the component pattern is basically you have a game object, which is just a generic object in your scene. And this has a list of components. And so the game object only contains something that every game object would have, which is like a transform and possibly a name. And so that basically means the transform is its position and size and everything, and then a name is just whatever the game object has. So then you basically just give it this component, which is another very abstract generic thing, and a component can literally be anything. So then you put all your pieces of logic for different types of things game objects can have into these components. And so you make this very wide hierarchy instead of very deep hierarchy, which is good. And so you have like a player component, you could have, in our case, a Goomba, a sprite, a collider, a font. And there is cases when it's okay to go a little bit deeper. Like in the case of a collider, I've found that it's easier to go one layer deeper and then have like a base collider that is also, you could have a box, a circle, or a triangle, and so on and so forth. But I think 3 or 4 layers is probably the deepest you should ever go with your hierarchies, because any deeper than that, and it poses a problem. But game developers started to see a problem with this approach as well. So if you are creating components willy-nilly everywhere, say you were going through your initialization phase and you're just starting to create components. So you create your game object, gets stored in memory here. Say you create a component, gets stored here, create another component, gets stored here. And so this is game object 1. Then you start creating game object 2, gets stored here, component 2 gets stored here. And this is like the best case scenario in memory. Typically, these would be getting placed in wherever they could, not like this. And then say you added another component to game object 1. Well, all of a sudden you have this gap. And this is memory fragmentation a little bit, but this is also conducive to cache misses, which is the big problem. So what you end up getting is you get these things scattered throughout memory. There is no logical pieces to this. And so what ends up happening is when you're looping through all the components for game object 1, you're actually having to go jump from memory to here, and then like somewhere over here. And that can actually cause some performance issues. And so this is something called a cache miss, because typically the CPU will try and load all the memory that's relevant into memory currently, and then it can draw it. So if the memory is physically closer, then it will run faster. But it has to load memory that it doesn't think it's going to be used into longer term memory over here, and then it can take longer to get that. And so when you start creating objects and components just anywhere, then you end up giving a very good opportunity for all these cache misses. So they came up with another design to fix this called data-oriented design. And the whole goal of data-oriented design is to break up your components into logical groups. So you would have all of your render components, all of your sprites here. You would have all of your box colliders. You would have them all in just a big array. All your game objects. So like this is just like your transforms. You would have them all in a big array. So you would keep all of them in logical arrays together. That way your memory looked more like this, where you had just big blocks where all the components are right next to each other. And you would have all the different types of components right next to each other throughout here. Which means that now your memory is very local, it is all close together, and you will reduce those cache misses. Then, instead of having an actual game object, you could have a game object, but typically what they start to do is they have these IDs. And so say ID 0 would give you a map to every single component that it has. So it would say, okay, it's index 0 in the transform, index 0 in the collider, index 0 in the sprite, and then so on and so forth. And each of these IDs would map to all of the different components that that game object has, so that you can look them up whenever you need to get them. But they thought, you know, we can do this even better. This isn't just the best design. There is still another better way to do this. Because typically, in games, you end up having these systems that end up using the same components over and over again. They have to get a hold of the 3, 4, 5 different components, and then all the other systems just need a few different components, and they don't typically interact with other ones. So this is where entity component system comes in. Instead of just having an entity and a component, you have these systems which typically need to grab the different components that they are controlling. So say you had a physics system, this would grab the rigid body, the collider, and then maybe some other stuff that is attached, the material, because it needs to know how bouncy it is or something. And then what you would do is you would store all of these in arrays next to each other. So the rigid body, box collider, and everything would be stored in arrays right on top of each other so that they are local. And then you would have something called a physics system. You could or you couldn't. It just depends on what you want to do. And the physics system, you could go directly to it and say, hey, give me the rigid body for the guy that I'm currently on. And then the physics system will go and index into the rigid body for your ID and give it directly to you, which reduces the need to go even farther out into memory. And then you do the same thing for rendering and for AI. So rendering, you would need sprites, you would need fonts, you would need textures. These are all different components that you could group together. For AI, you would need pathfinding, you would need enemy classes, you would need damage classes, weapon classes, all that stuff. You would put them all next to each other. And this increases your performance even more. However, there's a problem for us because we are coding in Java, and Java is a garbage collected language, which means that we have no control where these things get placed in memory. You can control it to a certain degree, I say, but not really. Even if you create arrays like this, one after the other, you have no guarantee that they will end up in the same memory space right next to each other. So for us to be thinking about ECS and to be thinking about data-oriented design, it's stupid. We can't do it. If we were going to move into a lower level language like C++, where we could say, give me a block of memory that's a gigabyte wide, and I will manually dictate the exact layout of this memory, then we could employ this technique, but we just can't. So we will be sticking to the entity component pattern because it's the only thing we can really do in Java. We have one more problem that comes along with this. Communication. So communication between components. I sort of talked about data-oriented. You have this ID, but still there's one more problem. How do you know when all the components are attached to the game object? So you have your game object, right? And it gets created. But say your rigid body needs control of a collider. When should it ask for a reference to that collider? When does it know it is there? And so the thing that I've typically done, which has worked fairly well, is this little life cycle thing that I have right here. And so basically I ask the question, is the scene currently running? If it's not, it's easy. First, we create all the game objects, and typically in an initialization method, so this would happen in init. Then for each game object, what we do is we add all the components. So we just keep adding components, adding components, adding components. Then we start all the game objects. So we know all the game objects have been added because we've loaded the level or something along those lines. So then we call this method called start on each of the game objects. And that start method goes through each game object and calls a start method on the component. Then that component can call get component for another component that needs. So if the rigid body needs the collider, it would say, give me a reference to collider inside of this method. Because it knows once it's inside this method, all the components will have been added. We will guarantee that. So this is where we would call for those references. Then we run the scene. What if the scene is running though? What if we're dynamically adding components at runtime? Well, typically I've found you don't add or remove components at runtime. It does happen. I'm not going to say that it doesn't, but typically what you're doing is you're creating game objects or removing game objects. And so in that case, it's still pretty relatively straightforward. What you do is you create the game object first, then you add all the components just like we did, then you add the game object to the scene. And once we add the game object to the scene, we basically say, okay, is the scene running? If it's not, then we don't have to worry about this. But if it is, we'll start the game object here, and then we'll do this thing again where it basically just says, okay, start the game object, and then for each component, start the component. So that's how you deal with that issue, because when we're editing levels and stuff, the scene is already going to be running, and we're going to be adding and removing game objects at runtime, so we must do it a little bit differently. But in terms of adding and removing components dynamically, it doesn't happen too often. Typically, you will know exactly what components you need for a game object at the object creation. It's rare when you don't, but if you do, you can come up with a special case just for that. And you don't even know if that component's going to need a reference to other components too. So it could be easier, it could be harder. But this is the approach that we will go through. So now that we sort of know a little bit about ECS and the different methods, and if you guys are programming in a different language, I highly suggest you try and do data-oriented design because it should increase your performance. I will have some reference articles too so that you guys can read up more on that in the links below. But let's code this system real quick, well, this pattern real quick, and get it working in our game engine. If you've watched my Geometry Dash tutorial, then this is going to be very familiar. I'm just going to run this real quick so we can see where we were at. Now, let's go into our Jade package. And inside here, I am going to create a new class called GameObject. This will be our middleman. This will be our container for communication. So we are going to create a function that will initialize this guy, and we're just going to say GameObject. And he's going to take nothing for now because, well, we can give him a name for now. But we don't have the transform data utility yet. So once we get to that, we will add that. So for now, we'll just say this dot name equals name, and then we'll go up here and we'll say private string name. And then down here, actually, we are going to also create a private list of components, just like I said, and we will just call this components. Then I am not going to import that from there because that's not the one we want. We will go into here and we'll say create a new class. We're going to call this component. And this is going to be an abstract class. So we will just add an abstract right here. And we know every component is going to need at least one method. And what is that method? Public void update with a float variable delta time. And this is abstract. So every component will have an update method that they can override. And then inside of here, what we're going to do now is we're going to create methods for adding and getting those components and starting those components. So first one we will do is get component, because that's the one that's a little bit weird because of generics and everything. So what we'll say is public t extends component t get component. We're returning of type t, and I have to look at what I did the first time every time I re-implement this, so don't worry if you don't completely understand this. Just know that it does work. But basically what we're saying is we have some abstract class t, and it is of type component. So we're telling Java, hey, we're returning some type, and it's going to be a possible subclass of component. We don't know how many layers deep. We just know it's a subclass of component. And we're saying we want to take in the class that represents that same type that we just said subclass is component inside here, so that we know what component we're looking for. Then what we can do is we can say for component C in components, what we will do is, I did not mean to do that. What we will do is if the component class dot is assignable from C dot get class. So if the class that we passed in is assignable from the class of the current component we are looking at, then we will return that class, but we have to cast it. So we'll say component class dot cast C. That way we get the appropriate cast, and we can also have our IntelliSense work with this, which is really nice. Then we're going to say catch the class cast exception. Oh, and we should actually wrap this in a try catch. So up here, we'll say try to return it. And if we fail, catch the class cast exception E, and we will say e.print stack trace and assert false error casting component. And I have never run into this error, so I highly doubt that you guys will too. We do not find anything that works, and the reason you shouldn't run into this error is because we're checking right here. So it shouldn't even, we shouldn't even have to do this try catch, because we're saying, okay, only if it's assignable, return the cast, but Java makes us put this catch in here. But basically, if we don't find one, we're returning null, because that is just the default that we will say. If we don't find it, it equals null, which is nice because it's nice to have that default, because there will be cases when you cannot find it. Okay, next thing that we will want to do, because this one is also kind of useful and we will probably need it, is say public t extends component void remove component class t. So same sort of method definition that we had right above there. That t object is just a generic that is of type component. Then we'll say is for int I equals 0 and I is less than components dot length or size I plus plus. And the reason I'm doing it this way is that we don't run into any concurrent modification errors, which is bound to happen, I'm thinking, with this. But we'll say if component class dot is assignable from c dot get class, same thing, where c is components dot get I. So if it is assignable from that component, then we'll say component dot remove, and then we'll give it the index that we are currently on, and then we will return. That way we don't end up running into errors by concurrently modifying this loop while we are running through it. So add component and get component, or get component and remove component, both pretty simple. Last one we're going to need is add component, right? Because of course we need that add component, and we will need a start and an update methods that we can start and update these objects as well. Add component is super simple. It's exactly what you would expect. So just add component, and we will take in a component C. We'll just say this dot components dot add C. Last thing we do have to do though is say C dot game object equals this. So we assign the reference to C's game object to this. So all components will have a reference to their parent, which is the game object, and we will make this public, and we will say this is game object. So just like Unity, basically upon adding the game object, or upon adding the component to the game object, we assign the reference to who this component is attached to. That way the component can then reference it whenever it wants. And we will initialize this to null because there is no guarantee that will ever be added to a component. So we want to double check and make sure that it does get added. So that's all we have to do for adding a component. And then last thing we want to do is create a public void update method. And this will take in delta time. So this is the game object's update. And what the game object is going to do is say for int I equals 0 until I is less than components dot size I plus plus. It's just going to say components dot get I dot update, and we'll say dt. That way it can update as it's going through. And then the last method we will need is public void start, and this will just go through every component, and we'll say for I until it's less than component size I plus plus. We'll say components dot get I dot start, and inside of component we'll go into here, and we will make start a concrete method that can be overridden if the subclass wants to, but they don't have to override start because that's not a method that is actually needed for that. There we go. So now we got our start, we have our update, we can add and get components. Now we should go into our scene and implement that functionality I was talking about, where we can actually start each of the game objects and then check and see if the scene is running. And if it's not, then we do a little bit of fancy work. So we'll say private boolean is running equals false. Then we will have a method down here called public void add game object to scene. And we will have another method up here called public void start. And this one will be called by the window class whenever the scene has finished initializing, and this one will be called every time a game object is added to the scene. So on start, we will say if it is not running, then what we want to do is say for each of the game objects. Actually, yeah, start should be called when it's not running anyway, so we don't need to call that. So we'll say for each of the game objects, GO in our game objects list, which we will create in just a second. We'll go up here and we'll say private list game object, game objects, and inside we'll just say right up here it equals a new array list. And then over here we will say for each of those game objects we'll say go.start. So when the scene is started, we start each of those game objects. Next, when we are adding a game object to the scene, we will say if not is running, then we should actually do nothing, because if it's not running, then this start method is going to get called. So what we should actually say is only if it is running. Actually, yeah, we do want to worry about something if it's not running. So, but we don't want to start the game object because it's still going to get started in there. So if it's not running, what we'll say is game objects.add, and then we'll take in the GO that it passed in. If you want to add a game object, you obviously have to pass it into the function. So if it's not running, we will just add it to our list, and we will let the start method handle starting the game object. Otherwise, if it is running, we want to add it to our list, and then we want to start it immediately. That way we know that it can call and get those references if needed. So those are the two cases that we had to worry about, and they should be handled within here. And now we can add game objects and we can start it. Let's go into our window and actually start the scene now. So after we initialize, we start. And I know this is a lot of steps in our scene creation, but it is necessary and it typically does help. This is the maximum amount of steps we'll have though, because any more than this and it starts getting confusing, you have to draw out charts and everything just to keep track of when things get started and when things are called. It's just a mess. So we'll leave it at this. Now let's go back into our level editor scene and let's actually create a game object. We will just call it up here. And we'll say this game object is our test OBJ. And inside of init, we'll say this dot test obj equals a new game object. Test object. Okay, and then we want to add some component to it. So let's go into here, say new package components, and this will house all of our components. Let's just create a new Java class. We'll call this sprite render, something we will be needing pretty soon anyways. So let's say this extends component. We're going to import it from Jade. It's going to say we need to implement that update method. We will implement that update method, and we will say system.out.println I am updating. And inside of here, we'll say at override public void start, and we'll say system.out.println I am starting. And actually, let's just print out update on the first iteration. So we'll say private boolean first time equals false, and then we'll just say if not the first time, then we'll print this out, and otherwise first time equals true, and then we will stop printing out. That way we can just sort of see the order of operations that all this is happening in. Then let's go back into our level editor scene, and we will say system.out.println creating test, we'll say test object. Then down here we'll say this dot test object dot add component new sprite render, which takes in nothing. Then what we'll say is this dot add game object to scene this dot test object. So now we have we've created it, we've added the component, we've added it to the scene. Then down inside of our update method, we will say at the very bottom for each of the game objects, geo in our game objects, and we'll make that protected so that we can access that in here too. We'll say geo.update dt, and let's go into our scene and make that game object list protected instead of what it was before. Also, right after we start it, we will say is running equals true, because we know that right after we start it, it should start running. Okay, yeah, so right after we start it, it should start running. So we'll just say is running is true in there. But yeah, so we update each of the game objects at the bottom of our update loop. And then what we'll do is we'll do one more test. So we'll say game object geo, which is our new game object. And then we'll say geo.add component new sprite render. And we'll say this.add game object to scene geo. And then we'll do a similar thing where we say if it's the first iteration, so private boolean first time equals false, and then we'll say if it's not the first time, then we'll do this, and that will fix that scoping error we have too. And we'll say first time equals true. Oh, that should be backwards, but whatever, it'll still work. So basically what we're going to do is we're going to add a game object at runtime too, just to see the order of operations for this too. And then we'll say print line creating game object, and it should be the same order. That's what I'm hoping for. So let's run this now, and we're going to get an error because we never initialized our components. So inside of here, when we are creating this, we'll say equals a new array list, just so that we don't have a null component list. There we go. And then we get it. And we see that it says I am starting creating game object. I am starting, I am updating, I am updating. Okay, yeah, so look, it says creating test object. This is exactly what we should be expecting too, by the way. So if we go to our level editor scene, it says creating test object right here. Then it goes through all this stuff, and then it says I am starting. Then it says creating game object down inside of our update loop. And then it says I am starting, and then they both update at the same time. So that's perfect. If we had moved this to below the update loop, then we would get an update, then create, then start, then another update. But what I want to show is that we get the same order no matter what, which is what we want. So if we add it at runtime, first it creates it, then it starts it. If we add it in the initialization method, first it creates it, then it starts it. All the same time, and then it starts updating. So we don't have to worry about order of operations. We have that all well and done. And one more component just to sort of rehash one of the other concepts I was trying to get at. I know this is going a little bit long too, so sorry about that. We'll create a font renderer class because that's something else that we will need eventually. We'll say extends component, and I'm going to import that from Jade, and I'm going to implement that method. Then inside of here, what I'm going to do is at override public void start, and we're going to say if GameObject.getComponent sprite renderer.class does not equal null. That's the last part of that. Then we'll say system.out.println found font renderer. And otherwise we'll say, actually we don't need to worry about otherwise because we're only going to have one. So if we find a sprite render, then we will print that out. And also another good thing about start, if you try and access GameObject inside of your constructor, GameObject is going to be null. And that's just because we have not assigned it yet, because there's no way we can possibly add this while it is being constructed. One of the bad things about constructors, I think everything should be handled in initialization and a start method like this, because it just clears things up. You know exactly when things are happening. Constructors and destructors kind of muddle things up a little bit. But basically, we will find the game object will not be null because we're in the start method, and then we know because it's already been created. And then we know that we will have a font render. So let's go into our level editor scene to illustrate this one. And right up at the top, we'll say this.test.obj.add component, new font render. And we will see that we should get found font render printed out too. So I am starting, hey, we found the font render. Then it creates the game object, says I'm starting, I'm updating, I'm updating. Okay, so we have our whole component architecture working. This is just entity component, not entity component system, but we can create components, add them to game objects. We can find other components from within one component using the game object as a middleman. We have completed this and it works nicely. And we can add objects at dynamically at runtime or statically inside of the initialization method. So that's about it for this tutorial. We're going to start using this now to create some higher level functionality where we actually use this sprite render to display the graphics and stuff instead of manually doing everything inside of the level editor scene. So we can offload all of this to some different aspects of our game engine, which will be nice because then all we will have ideally is this for game object in game objects at the end of this. If you remember in the last tutorial, we talked about an entity component system and started getting some of our higher level stuff set up so we can start reducing the amount of boilerplate code that we have inside of our level editor scene. In this tutorial, what we're going to be doing is offloading our VAO creation and everything in our mesh creation to a batcher. So we will be creating a render batcher, and we will be batching up to 1,000 quads or however many you want into the game, which will reduce frame rates from what could be 1 frame per second literally all the way up to 60 frames per second. So we will be learning how to do all of this, and first I'll explain exactly what batching is, and then we will go over in code and see how it all works. Okay, so let's try this and see if we can get it done. Before we begin coding, let's discuss what batching is. So in 2D games, you have the advantage of knowing that you are dealing with very simple geometry nearly all of the time. What I mean by that is you can literally represent your entire game using nothing but sprites, which are essentially just 4 vertices and 2 triangles and 1 square. Literally, that is your entire game world. Even more complicated things like this down here, this is actually just a semi-transparent sprite. And so using this fact, we can now say, instead of drawing all of this one by one, what we would typically do is say, okay, draw this one, then draw this, then draw this, then draw this, so on and so forth, until you end up drawing every single one. That is very, very slow. So instead of that, what we can say is, okay, we know every single thing is going to be in the form of this, so let's batch it together. Let's make one giant mesh where everything is interconnected, and it looks something like this, and we'll support up to 1,000 squares per mesh. And then we do, okay, now we can fit all of this into one draw call, and we end up drawing one. I did some performance testing, and 10,000 squares without batching gives you 1 FPS. 10,000 squares with batching gives you 60 FPS. So this is essential if you want a functional game. It really does help things out a lot, and you don't have to do much to check and see that it does a lot. But how do you do this? How does batching work? Well, like I said, we know that everything can be represented by squares, by these quads, which we know from previous tutorials is just 2 triangles. Well, we also know that if we order the vertices in such a way, v0, 1, 2, 3, then we can order them into, we can just stuff them into one big array, right? And then we're going to upload this to the GPU anyways. Well, let's say, and this is the actual format we're going to use, we want to have position X, position Y, and then R, G, B, A, so the color. So we'll have position for each vertex, and color. So this would be like the position here in the world. And that's what we want for every single vertex. Then we know that the way we would order this to draw it correctly for the elements, so this is the triangle order, we would say, well, we need to do it in counterclockwise order. So let's do 3, 2, 0. We do this vertex, and this vertex. That's the first triangle. Then 0, 2, 1, which would be this vertex, and this vertex. Second triangle. And it's in counterclockwise order, which means it will show up correctly. Well, let's say we have a second sprite that we stuff into this vertex array. What do we do then? Well, as long as we're stuffing it in this order, V0, 1, 2, 3, then we do 4, 5, 6, 7, the same exact order. We know it's going to go 7, 6, 4. We just do the same thing we did last time. And 4, 6, 5, which is just this, then this, and this. And if you notice, this is the same exact thing as this, except with 4 added to every single element. So what this tells me is that these elements you can generate automatically, which we will do, and you don't have to worry about them ever changing. Whereas these vertices could potentially change. If your sprite is Mario, you know that the X and the Y are going to change quite a bit. And if we had a texture in here, the texture coordinates would change a bit too, because he's constantly being animated. So what that tells me is we can generate this one once, upload it to the GPU, never have to change it. And we know exactly the format it's going to take, because as long as we stuff in the vertices in the correct order, it will always take on this type of pattern. And then with our vertices, we can just upload once with our initial set of vertices. And then every time some of them change, we can go into the array, specifically change that vertex, and then re-upload that specific portion, which is the whole essence of batching. So this is the format we're using. Now, I think you guys can probably do most of this on yourself. If you want to give it a try, this is exactly what we will be needing. We will have a couple other helper functions and stuff, but this is the gist of the most important stuff. We will be creating a renderer class, and this renderer class will have two main functions: add game object, which will take in an object, and then render. So this will also contain a list of render batches. And render batches are this next class that we will be creating. And a render batch is where all the heavy lifting is going to happen. It will have a start method. This is where we create the VAO, the VBO, and the EBO. So all that work we're doing in the level editor scene will be stuffed into here. We will have an add sprite function, which takes in a sprite render and then adds that sprite to its own list of sprites, which we have right here. And that way it can figure out if any of them are changing or not. Then it has an int array, generate indices, which we said up here is always going to be the same. So we can generate those once, these guys, and we know that's never going to change. Then you have your render function, which gets called by this render function when it's going through all of its render batches. And lastly, I have this helper function, load vertex properties int index, where it would basically say, okay, so say you want to load vertex 0's properties, you would say load vertex, you would say load 0. And then it would go and it would create 4 of these. So x0, x1, x2, x3. Because it would be loading in every single one of these vertices, because this is one sprite. This is one quad. And then it has a shader for rendering, and it has a float array which contains all the vertices, and it has a VAO ID and a VBO ID. So let's actually try and code this and see if we can get this all figured out now. So before we begin doing the render stuff, we have to do a couple more things that are going to be essential for that render. One of them is creating the transform for our game object. So we'll create a new class in here, call it transform. And transform will very simply contain a couple of public variables. So we'll have a 2f for its position, and we will have a public vector 2f for the scale. And then we'll take in a couple of different methods that can initialize it. So we'll have one that just says this dot position equals a empty. So this will initialize it to 0, and this dot scale equals this, which is just empty again. And actually, let's pull this out into an init function because this always simplifies things a little bit more. So we'll say position and vector 2f scale. This is what I typically do if I have a function that I want to overload. I'll have one main function, and then I will have several that just call this main function. So we'll just say this dot position equals position, and this dot scale equals scale. And then inside here, we'll say init new vector 2f, new vector 2f. Then we can give it public transform vector 2f position. If they just want to supply the position, then we'll copy this, and we will pass in position. And then we will do one more that takes in position and scale. So we'll say public transform vector 2f position and scale. And then we'll just say init position and scale. All right, there we go. So now we have our transform, which should allow us to publicly access these variables, which will be very helpful. Next, let's actually add this to our game object. So we'll go up here and we will say public transform. And this will be like one of the only public variables we have, which you'll see why in a minute too. We'll just say this dot transform equals new transform in here. And then we'll say public game object string name and transform. Then we'll just copy this and do it here. And we could do the same thing we just did back there, creating an init function and stuff, which I would suggest, but I'm trying to get through these things kind of fast. Then let's go up to our sprite render. Since we will be using this, let's delete that code we had before. We no longer need to know about this stuff or this stuff. And then inside of here, what we're going to do is we're going to say vector 4f color, because we are going to be taking in a color now. And we will have a vector 4f here, which is the color, and we'll just say this dot color equals color. And since this is going to be private, we will need a way to get that color. So we will go down here and add in a public, not private, vector 4f get color. And this will just return that color. So this is all stuff that's not super complicated, but it's stuff that you just need to get done. Okay, last couple things that we have to get out of the way. Let's go to our window and create a getScene function. This will also be very useful because there are many times that you just want to get whatever scene you're operating on. So we'll say public static scene getScene return get.current scene. Very simple, but it will be helpful in a ton of situations. And then the last thing that we're going to do is go to our scene, and we are going to add a camera function that just gets whatever the camera is. So we'll say public camera return this dot camera. All right, so I promise that's it. Now we can start going on with the actual render batch stuff. This was all important though, just that we can get it all done very easily. So let's go into our render now. We'll create a new class and we will call this render batch. So like you saw before, this is what is going to contain most of the heavy lifting, and it's going to be doing pretty much the majority of the stuff we need. So what I like to do inside of these batches is define the layout of my vertex. So we can't really create these things called structs, which are very helpful in C++, which allow us to do this. So I like to just define it up here so I know exactly what it should look like. And in our case, we're going to have a position and then a color, which will just look like this. We will have position, which is 2, and then 4 colors, 4 floats for colors. Then, just like we were doing inside of our level editor scene, we're going to create these final ints called basically the size and everything, so that we just know the size, the offset, and then the vertex size and the vertex size in bytes. Just like we did, if we go into the level editor scene, we did all that right here. And it's the same concept we're doing, except we're just going to do it once because we know exactly what the layout is going to be and we never have to redo that. So we'll say the pose size, there's 2 of them, private, final, and color size. Well, there's 4 colors. And then we'll say private, final, and pose offset. Well, that's 0. The position starts at offset 0. Private, final, and color offset equals pose offset plus pose size times float dot bytes. So remember, the offset is in bytes, and we know that the offset for color starts here, which is 2 plus however big a float is. So the pose size times bytes, which gives us the correct offset for the color. Then we'll say private, final, and vertex size. The total size of our vertex contains 6 floats, and we will finally do one more, the vertex size in bytes, which is just the vertex size times float dot bytes. And that will just allow us to pass everything in very easily, and we'll be able to read it and know exactly what's happening. We'll need a couple more things. Like I said, we will need the sprite render, and we'll just create an array of sprites because we'll know exactly how many sprites one batch should take in. Int number sprites. This is how many sprites we currently have inside of our array. We'll have private boolean has room. Do we have enough room or not? Private float our vertices. So this will actually contain all of this vertex information, literally just stuffed inside of this giant array. Then we'll say private int VAOID, VBOID, and we are going to create the EBOID and EBOID inside of the start method, which we will do in a second. And we'll need a max batch size and a shader. Okay, I know this seems like a lot of stuff, but I promise it's all necessary, and it will all make sense as we go through and sort of pull stuff out and redo everything. Now, when you create a render batch, what we want to do is pass in a max batch size, which will tell us how many quads we want this batch to be able to hold. So that way we just know exactly how much we're going to use. Let's create our shader in here too. We'll just say shader equals the new shader, assets slash shaders slash default.glsl. So we'll just pass in the default shader we've been using. I'll say shader.compile. Then we will say this.sprite equals a new sprite render. How many will we hold? Well, we will hold max batch size, of course, right? Because that's the maximum amount of sprites that we will be able to hold inside of this sprite render. So we just create an array that big. Then we'll say this.max batch size equals the max batch size. Then we need something else. How many floats will we need for our vertices? Well, we know that each sprite will contain 4 vertices because they are one quad. And we know that each vertex has 6 floats, which is stored in this vertex size. So using that information, we know that we will need max batch size times 4 times vertex size, because we have 4 vertices per quad, and then we have max batch size sprites possible, and we have vertex size floats in one vertex. So that should give us the correct amount of vertices that we can hold. Then we'll say this.number sprites equals 0. We don't currently have any, and this.has room equals true. We definitely have room since we have 0 sprites contained inside of this. Next function we want to do is create the start function. So this is where we will create all the data on the GPU. So we're going to allocate room on the GPU and say, hey, this is where we're going to be working with. Please give us enough space, and it will do that. So first thing we're going to do is generate and bind a vertex array object, just like we did in the level editor scene. We'll say VAOID equals GLGen vertex arrays. And what this does is it generates a vertex array object ID for us that we can use. And then we will say, give us or bind that array object because we will be using it. So we bind it to our GPU. Then we'll say allocate space for the vertices. We kind of have a quagmire here, right? We want to start it, but we don't have any sprites. We know how much space we're going to need though, which is all the GPU needs. As long as you know exactly how much space you're going to need, it can allocate that space for you, and then you can use it when you're ready. So what we will say is VBOID equals GLGen buffers, and let's import that. So we generate that buffer ID, then we'll say bind the buffer. So this is going to be an array buffer, and we're passing in the VBO ID. Import those. Then we will say GL buffer data. So this is the one we used when we actually had data, but we don't now. And if you notice up here, it says we can use this one, which says it takes in a target, the size, and whatever your usage is. So I'm going to get this out of the way. We can tell it, okay, we know that we are going to need vertices.length floats times float.bytes. It needs it in bytes. So we know we need this many floats at least, and we know the size of one float in bytes is this. And so that is what we pass it, and it will allocate that space for us. And then this is the last thing that may be different. Instead of static draw, we're going to say dynamic draw, because remember, our vertices can change. So we need to tell OpenGL, hey, we are going to be changing this in the future. Make sure you put it in a place where we can read and write to pretty efficiently. And that's what that does for us. Next, we're going to create and upload the indices buffer. So we're going to say int EBO ID equals GLGen buffers. And remember, this is just so that we can reduce vertex duplication by indexing when we are drawing our quads. Just like I showed you with those triangles, we had V0, V1, V2, all that stuff. Then we'll say int indices equals generate indices. Remember, the indices are never going to change, so we'll be able to generate them, which we will do in a minute. Let's finish uploading our hypothetical indices to the GPU first, though. So we'll say bind element array buffer, and then we will say EBO ID is the ID that we are binding to. Then we will say buffer data, GL element array buffer, and the data we're buffering is our indices. And we can say that this is GL static draw. We know we are never going to be changing the indices because they will always remain the same. So we can tell GL, you can put those wherever you want, whatever's best for you. And it doesn't have to worry about us writing into it. We just need to read from it. So that's what we do. Then we will enable the buffer attribute pointers, which are basically just telling it how our vertex is laid out. So vertex attribute pointer 0 is going to be our position size. It's going to be a float, and let's see what else it takes in. And normalized is false. The stride will be our vertex size in bytes, and the pointer will be pose offset. So that's our offset for us. Then we can say GL enable vertex attrib array 0. So we will enable that vertex attribute right after we do that. So just so you can see, that's what we're doing. Then we're going to be doing basically the same thing, except for our color now. So we'll say GL vertex attribute pointer 1, and this is going to be our color size. This is going to be a GL float also. It's not normalized, so false. And the stride is going to be vertex size in bytes again. And the buffer is going to be color offset, or the pointer, not the buffer. And then we'll say GL enable vertex attrib array, no, not array, pointer, attrib pointer 1. And what we're doing here is literally the same thing that we talked about. Up here, we want our vertex to look like this. And so now we're telling the GPU, hey, we want our vertex to look like that right here. That's what we're doing. Now let's create this generate indices function, which is actually pretty simple because like I said, they follow a very strict pattern, which makes it easier for us when we're generating them, right? So we'll create this function, private int generate indices. And we're going to say, okay, we have 6 indices per quad because we have 3 indices per triangle. So that lets us know how big the array has to be. So we'll say elements equals a new int, and we'll say 6 times the max batch size. We can have up to 6 indices per sprite, and we can have this many sprites. So we will allocate enough space for that. Then we'll say for int I equals 0 until I is less than max batch size, I plus plus. And what we're going to do is we're going to create another helper functions, load element indices. We will pass in our elements and the index we are currently at. So now what we will do to load the element indices, we'll say private void load element indices, which will take in our int array elements and our index. And this will modify this array inside here, which is why we don't have to return anything when we pass this array to here. it's passing a reference, which means whatever we do to it in here will actually change it in here as well. So what we need to do is we need to find a couple of offsets. So we're going to say offset array index equals 6 times index, and int offset equals 4 times index. And what this basically means is, remember I was saying that we have our triangles, and they look like 3, 2, 0, 0, 2, 1 for the first quad. The next quad is 7, 6, 4, 4, 6, 5. Well, we have a couple offsets we need. So if we're looking at quad 1, which would be this one, we know that the offset in the array is 0, right? So we would do 6 times index. So this is the 0th element, which would give us 0. Then we need the offset for the start of this number. What is this first number? Well, that's 0, so 4 times index. Then it makes more sense if we do this one. 6 times index, this is the first one, so we would get 6, which means that would be 1, 2, 3, 4, 5, 6, 7. If we start from 0, 6, which is this index, then the offset is 4 times 1, which is 4, which is the number we need right here. So that's basically all these mean. You can leave that comment in there if it helps you out when you're thinking about it. So we'll say creating the first triangle, triangle 1, which is 3, 2, 0, and then we need 0, 2, 1, which is triangle 2, will be elements offset array equals offset plus 3 offset array index. Sorry about that. Then we'll say elements offset array index plus 1 equals offset plus 2. Elements offset array index plus 2 equals offset plus 0. And you can see what I'm doing. 3, 2, 0, 3, 2, 0. And we're just going up 0, 1, 2, 0, 1, 2, the index into this array, and then the numbers we want at that position. So literally just taking that pattern and copying it multiple times. Then we'll copy those and do one more, and then we'll say this is going to be 3, 4, and 5 for triangle 2, and the pattern is 0, then 2, then 1 for triangle 2. Then we can be done. So this will load the element indices for whatever quad we are currently working on. So now we have that done, we can say after we finish loading every single quad, we will just return the elements, which will give it to him, and then he can actually bind it and upload those vertices. That should be the only time we ever have to call that. Now, let's assume we have data inside of our vertices. Let's create a render function, because this is the next kind of easy step. I'm going to say for now, for now, we will rebuffer all data every frame. Remember how I was saying that we could change it so that we could rebuffer only a sub-portion of the data? If only one vertex changes, we only have to change that vertex. Well, we can, but it's a little bit hard to do. So we will save that for a future tutorial. For now, what we'll say is we're just going to rebuffer the whole vertex array every single frame, which is still faster than one draw call per item. So we'll say bind the VBO ID. This is why we held on to that ID. And we're going to say buffer subdata, even though technically we're buffering the whole thing. GL array buffer. Now let's get rid of this thing so that we can actually see. And it asks for an offset, which is 0. Then it asks for the data, which is our vertices. And then it asks for nothing else. That's it. So basically what this does is it says, okay, I'm going to buffer some data into this VBO that you guys gave me, this buffer. And we want to buffer our vertices starting from 0. And then it will just upload all the vertices starting from 0. So that should be good for that. Then we want to make sure we use our shader. If we go into our level editor scene, we are basically doing everything we did inside of this update function right here. We say upload, blah, 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 use the shader, do all that stuff. Except now we're just moving it in to our render batch. So we'll say shader.use. Then we'll say shader.upload mat for F. This is going to be our U projection, just like in the level editor scene. And we'll say window.getScene.getCamera, or just camera.get projection matrix. So that's why we created those helper functions. Very useful now. Then we'll say upload another mat4f. This is going to be our U view. And we're going to say this is the window.getScene.camera.getView matrix. And that should be good. That's all we need. Then we'll say bind the vertex array, our VAO ID, which is the VAO for this big batch. Then we'll say GL enable vertex attrib array 0, duplicate that. We also want to enable 1. Then we will draw the elements, which is just GL triangles, like we did in the level editor scene. And we will say we want to do this dot number of sprites times 6 indices per quad. And we have number sprites quads that we want to draw. That's how many sprites we have. And our type is unsigned int. And we will say 0 for our offset, which is the indices. I believe that's offset. I'm not actually sure what this one does, but yeah. Okay, we're good. So we draw the elements. Then we want to disable everything. So we'll say GL disable vertex attrib array 0. Duplicate that 1. We want to say GL bind vertex array 0. Unbind everything and shader.detach. So we just reverse everything we just did. We said use bind. Now we're saying disbind, unbind, detach, everything. And that should draw whatever's in our vertex buffer. Last thing we have to worry about. We have all the data and stuff, but we don't really have any way to get a sprite into this vertex array, right? We're never placing any data into this VBO. I mean, we are here, but we're never placing it into our local copy, this thing. So the vertices are always just a bunch of zeros. We want to fix that. So we will create another function, which is going to be add sprite. And this will allow us to add data to that array. So we'll say public void add sprite, and this will take in a sprite renderer, SPR. We'll just call it that. So first thing we're going to have to say is get the index and add the render object, which in this case is a sprite render. So index is basically where do we want to put this, and we want to put it at the end of our current array. So if our array currently has 5 sprites, it would be like 0, 1, 2, 3, 4, 5. The 5 sprites would be up to here. So then we would say, okay, well, the length is 5, so that will give us the next index in the array that we need, which is basically why we say the number of sprites is what we want. Then we'll say this dot sprites index equals the sprite. So we put it into that array, and it will say this dot number sprites plus plus. So then we increment it so that the next time we add one, it will be in the next slot. Then we want to add the properties to local vertices array. So we want to add all those float properties. So we'll just say we're going to call some magical function load vertex properties index, which we will create in just a moment. And then last thing we want to say is if the number of sprites is greater than or equal to this dot max batch size, then this dot has room equals false. Just so that we make sure we're updating that. If we have filled up our array, we want to make sure that we tell them we have no more room inside of this batch. So how does this magical load vertex properties function work? Well, let's go below our render function. We will create it right here. We'll say private void load vertex properties, which just takes in an index. Well, this is basically, we need to create 4 vertices per quad, and this is where we're going to do it. So first of all, we're going to say sprite render spret sprite equals this dot sprites index. So we're grabbing that sprite we just created and passed in. Now we want to say find the offset within array. There's 4 vertices per sprite. So the offset within the array is going to be index times 4 because there's 4 vertices per sprite. So equals index times 4 times vertex size because there's this many floats per vertex, which is in this case 6. So basically, remember we have float, float, and then we have float, float. So we have the position, then the color, and we know that's this size, and then we know we have 4 of these per sprite. So then the total offset, wherever we are inside of this array, this will be like the next one, would be the index times 4 times vertex size, which will give us the appropriate number. So that's the offset. Then we'll say vector 4f, what's the color we have for this sprite? Well, that's just sprite.getColor. So that one's easy too. Now this is the kind of confusing part, but we'll go through it step by step. We want to add the 4 vertices with the appropriate properties. And you could go and do this manually, but we could just loop over and do this a little bit simpler. So what we will do is we'll say float x add equals 1.0f, float y add equals 1.0f, and then we'll say for int I equals 0, I is less than 4, I plus plus. So we know that our vertices are going to be, we're going to have 1, 2, 3, per quad, right? We have top right, bottom left, top left. And what I'm going to do is I'm going to say, okay, we're positioning everything according to, I think, either the bottom left or the top left corner. I think it's the bottom left corners we're positioning everything from. And the way we control that is we're saying we're going to add the top right, 1.0, 1.0. Then we're going to add the bottom right, which we'll say if I equals 1, then y add equals 0.0f. So on the first, once we add the top, then we will go to this one. Then we're going to add the bottom left. So then we'll say else if I equals 2, x add equals 0.0f. Then we're going to add the top left, which we're going to say else if I equals 3, y add equals 1.0. And basically we're just going to use these numbers to figure out exactly how far. Because if we use 1 and 0, then we can say, okay, well this is going to be from wherever we're positioning it, it's going to be the width, so whatever that is, plus the position. So the width times x add plus the position, and that will give us the appropriate coordinates. If that doesn't make sense, please leave a comment, and I may post a follow-up video because I have to go through this kind of fast. So we're going to say load position first. We're going to say vertices offset equals sprite.gameObject.transform.position.x plus x add times the sprites gameObject.transform scale.x. Whoops, scale.x. And this will give us the correct offset no matter what, because x add will be 0 or 1 depending on which one we're actually adding. Then I'm going to duplicate that, and we're going to say offset plus 1, and we're going to do the same thing except for y, and we're going to use y add, and we're going to use scale.y. And that will make sure that we order the vertices in the correct order. Then we're going to load the color in. So then we're going to say load color, which is going to be vertices offset plus 2 equals color.x. Duplicate that a few times. We'll say y, this is z, and this is w. And then we'll say going up 3, 4, 5. Okay. And then lastly, we will say offset plus equals vertex size. What this does is, remember we said we wanted x, y, then RGBA. That's exactly what we're doing for every vertex. And then for every quad, we're adding 4 of these. That's why we're looping, and we're incrementing x add and y add so that we get the appropriate vertex position. It's a lot, but it should work, and we still have quite a bit to do. So let's get that done real quick. Now let's go into our render real quick, and we're going to create a new class. This is going to be called render, which will actually render all the objects. And we're going to give it private final int max batch size. I'm going to say is 1,000. That should be good. And then we're going to need a list of render batches, and we're going to call this batches. Then we're going to say public render. When we create it, we'll just say this.batches equals a new array list. So this is what's going to be in charge of submitting it to the appropriate batch and everything. So we'll say public void add. This will take in a game object, go. And what we're going to do is we're going to say sprite render SPR equals go.getComponent sprite render.class. And we'll say if SPR does not equal null, so if this game object actually does have one, we'll add it to our render. So then we'll say add SPR. We'll create one more function down here, private void add. This will take in a sprite render SPR, ITE sprite. And then what we're going to do is we're going to loop through any current batches we have. We're going to say added equals false. We have not added it yet. We're going to say for render batch in our batches. So in the batches that we have, if the batch dot has room, which we will create in just a second, then we'll say batch dot add sprite, and we will add in this sprite. And we'll say added equals true and break out of that loop. So if it has room, we can add it. If we get to the end and we did not have any room, we were not able to add it, then we'll say we'll create a new batch. So we'll say render batch, new batch equals a new render batch, which takes in the max batch size, which we conveniently have at the top of this class. Then we'll say new batch.start. We will start it immediately, and we'll add it to our list of batches. So we'll say batches.add this new batch. And finally, we will add in this sprite that we wanted to add. And that will actually add a sprite to our batches successfully. Let's go back into our render batch, create that function real quick. We already have has room inside of here, so we'll just say private boolean has room. Return this.has room. Very simple. Make sure to make this public. We don't want that private because we do want outside classes to be able to use it. Lastly, we want to create our render function, which is just going to go through each of the render batches, render batch in batches, and it's just going to say batch.render. So this one is nice and easy. It's pretty straightforward. We just add it to an available batch, and then we just create a new batch if we need to, and then we render. Not too much going on here. Now we want to actually add this to our scene so that we can add some stuff and see if it all works out right. So at the top of our scene class, we will go up here. We'll say private renderer, which is just that class we just created. We'll import that. And then inside of the start method, we will say this.render.add go. So this will be called at the beginning of the scene when the scene is being started, and then it'll loop through all the game objects and start them, and then we can add it to the render. If the game is running, we want to make sure that we also add it. So we'll say this.render.add go. So if we are adding a new game object to the scene while the game is running, we can add the game object to the render right down here. That should take care of adding the game object to our render now. Finally, we can go into our level editor scene and clean this up. So I'm going to go through here, delete all of this, except for that game object loop. Like I said, that's the only thing we want to keep. Delete all of this. And I know this might scare some of you, but it's fine because we offloaded all of this. Delete all of that stuff. This is so nice, much cleaner for our level editor scene. We can even go up here, delete all the imports that we don't need anymore. Inside of init, let's create something to test this batch render that will render 10,000 squares. So inside of init, we'll say, whoops, this dot camera equals a new camera because we have to initialize that. New vector 2f00, that's fine. Int x offset equals 10, int y offset equals 10. We want a buffer of 10 for padding or whatever. Float total width, this is going to be the total width of the square. We're going to say is 600 minus x offset times 2. Float total height equals float 300 minus y offset times 2. Don't worry if you don't understand what I'm doing. I didn't really understand what I was doing either. I just sort of messed with things till it worked. And it's fine because this is just test code, so it doesn't really matter. And we're going to say size y equals total height over 100.0f. Then we're going to loop through and we're going to say int x equals 0 until x is less than 100, x plus plus. For int y equals 0 until y is less than 100, y plus plus. So we're going to create 10,000 objects, 100 times 100, 10,000, I think. And then we're going to say float x pose equals x offset plus x times size x. This is the position inside of our game world. And we're going to say y pose equals y offset plus y times size y. Then we're just going to say game object go, create a new game object. And we're going to say this is obj plus x plus y with a new transform, new vector 2f. We're going to say x pose, y pose for the position, and then new vector 2f for the scale. We're going to say size x, size y. So we'll just create a new game object like that. Make sure you don't have any syntax errors. And then we will go.add component, new sprite render. We're going to say new vector 4f. We're going to say x pose over total width, y pose over total height, 1 and 1. So that's the color we're going to use, which is going to be based on its position. So we should get a nice gradient. And then we'll say this.add game object to scene, go. And that should be it. We should be good. And then finally, we will want to render it. So we'll say this.render. And we need to make that protected inside of our scene. So let's go up here, change this to protected. And we should be good. So let's hit run, and hopefully we get the square, but we're going to get an error. So let's see what's going on here. And it's saying render is null. Do we ever add? We don't ever add this, I don't think. So we'll just say up here equals a new render, and that takes in no parameters just to initialize that inside of your scene class. There we go. We get a picture. Right now it's black. Why the heck is it black? Well, remember our default.glsl. We did a couple things, so this isn't going to work properly. Remove layout location equals 2 in here, and we will remove f text chords take out f text chords here. This should all be good though. We'll take out time and the sampler, and we'll take out f chords here. And instead of doing this, we'll just say color equals f color. So we were sampling from textures before, which is why it was black. But now if we use the color passed in, we get this nice gradient, which is awesome. Last thing you can do just to see and know for yourself that this really is doing a lot. If we go back into our level editor scene, you can print out the FPS just by saying system.println FPS and then doing 1.0f over dt. That should give us the frames per second. So if we do that and we run, we see we're running at 60 frames per second on my machine. You may be running at something different depending on your refresh rate of your monitor. But if we change our batch size, let's go into our render and let's change our batch size to just 10 even, okay? This is going to slow it down dramatically because there's 10,000 triangles. Actually, it still runs pretty good. Well, let's bring it down to 1 and then you'll see what I mean. Okay, so now it's starting to take a minute for my computer, and now I'm getting 2 frames per second because it's doing 10,000 draw calls per frame, which just is not good. So just by increasing this to 1,000 quads per batch, we increase our frame rate from what would have been 1 frame per second if we had been drawing 1 square at a time to 60 frames per second. This helps tremendously. This is super important. Yeah, this is why we needed batching. It actually does create a significant performance improvement that we can see immediately. There are problems with our batching routine. There are things that we will have to fix along the way, but this is the gist of it, and we will add the new things as we go along, things like textures and stuff like that. In the last episode, what we did was we went over batch rendering pretty quickly, I know, but we had to get through it, and I will explain that in a little bit more detail in some future tutorials as well. In this tutorial, what we're going to be doing is resource management. So not sounding like a very fun topic, but it is crucial to game development, especially because if you are not managing your resources, then you can quickly run into problem with lag. So that's what we're going to be doing, making sure we're not creating a bunch of resources that we don't necessarily need, and we will have one central place to get our resources from. And that'll be like textures, shaders, fonts, all that type of stuff will be inside of our resource pool, you could call it. So let's see what our resource manager, why we need it, and then we will see how to create it. As many of you may know, Java is a garbage collected language, meaning that anything you allocate in memory, Java does for you automatically, and it consequently also frees that memory when the appropriate time comes. So say you create some variable foo, and this variable is of some size bar, which could be megabytes big, which would be huge, or it could be just a few bytes big, which is probably more typical. Then Java will put this onto either its stack, or if you allocate it with the operator new, which is how you create new classes, it will allocate it onto its own heap, its sort of virtual memory space, which would be somewhere farther out. Now, we don't know the specifics of this. I mean, you can know. If you look into the Java virtual machine and see how it runs and everything, you can figure out exactly how all this works. But basically, what happens is Java uses some complex garbage collection algorithm, which traverses some tree, checking to see if certain variables are alive. And it traverses this tree, which can go through thousands of variables, until it finds some dead ones. And at some time not known to us, it will collect all the dead ones and delete them out of this memory space so that it now has more memory space to work with. And that is the scary part for game developers in Java, because when that collection starts to run, your game will hit a massive lag spike. And there's nothing you can do about it. You can't control exactly when it runs or anything. And so that's one of the main reasons most game developers don't go with garbage collected languages, is because of this exactly. It's just not optimal. It's not something you want happening in your game. But there are some things we can do to kind of alleviate it, which is why I'm always so conscious about what I'm doing with my memory, because even though it's a garbage collected language, you need to be conscious of what you're doing with your memory. So every time you create a new class using the new operator. What Java returns is not the actual object, but a reference. So say you have some class, game object, right? This is our game object class. So we'll say this game object lives right here. Now, when you create this game object and then you say like my game object, I'm abbreviating, GO equals a new game object, what Java returns to you is this arrow. It basically says, okay, here's the memory space where this object is living. And this is something called a reference. Java does this silently. We don't even know about these. We don't know the difference between references and variables. Basically, if you had created an integer, a equals 5, what it returns is 5. But here it returns some hexadecimal address that basically represents some memory space where it's at. And so this address is basically the memory space that this object lives at. And then we call accessors on it, so any sort of method. And what it does is it says, okay, I'm going to go to this memory space and call this method on this object. So what this means, if we have big objects like pictures and textures and shaders and sounds, these are all relatively big files. They can be literally megabytes big, depending on the picture size and stuff. So these things can get very big. And so what Java will do is return to us a reference. And what we would ideally like to do is just hold on to this reference, because typically the reference is 1 byte. So that is way smaller than any typical picture size. And if we have the same picture being used in several places, we would rather pass around a copy of this byte than a copy of the whole picture. And so this is where resource management comes in. This is the whole reason we're trying to manage these resources. So what we do is we create a class, and I'm going to call this asset pool because that's what I called it in the last one. So just to make sure we're on the same page, we will call this asset pool. And this class will have a bunch of static hash maps, which have a string hashing to some object. And that object can be a texture, a shader, a whatever you want it to be. And so basically what we're going to be doing is making sure these never die. So Java will never garbage collect on them, which means we will never have hit that giant lag spike. Not really. There's still other ways we can hit it. But we will have a little bit more control over that. And we will also make sure that we're not copying huge amounts of memory every time we need a new picture or something, because instead of that, what we will be doing is we will be copying the reference to this object, which is actually stored here. It's just a reference. It's not the actual object, it's just the reference. And so we'll be copying around 1 byte of data instead of several megabytes, creating a new object every time somewhere else in memory. And so this is basically the whole aim of what we're going to be doing. And it's really simple. The way I do it is just a bunch of hash maps, like I said, with a string going to an object. That string is usually the file path, because files are typically the things that you will want to have managed as resources. Those are your resources, right? Typically, you could have other things, but we'll stick with just mainly our files and stuff, which will be our resources. This is what we're going to be doing. We will just be creating a bunch of hash maps. Let's try and code this so that you guys can actually see how this works. And then we'll start transitioning some of the stuff that we've been doing as objects to this. Now that we're back in our project, before we do start, I do just want to mention I changed like the background color and the position of these squares, but that's it. It didn't really change anything else in the code. And that should be minor. Like, that's just test code anyway, so it will be removed in the future. But anyways, let's move on. And what we are going to do is create this thing called an asset pool. And where should we create that? Well, this is sort of a utility function, right? An asset pool is for our convenience to store these assets in a good manner. So we'll create a new class, call it asset pool. And up here at the top, this is going to be a completely static class. So what we're going to do is we're going to make a private static map. The reason we're making it private is because we don't really want other classes to access the maps directly, because we want to be in control inside this class of exactly how they get added and how they get retrieved. That way we have complete control over it. So what we'll say is we have a map from a string to, and we'll start with a shader. So our shaders will be our first assets that we will be loading inside of our asset pool. And I guess it's kind of weird to think of a shader as an asset, but it is. I mean, it's a file that we're loading into memory. And The way I have it, we are hanging on to all the source code in memory. We might change that in the future because it's not really necessary. But anyways, we'll just say this is a new hash map. And you can hit Alt-4 to enter to get all those imported. Oh, and we need a name for this too. Let's call this shaders. So our shaders, and it's a new hash map. Let's go down here, and what we're going to want is we're going to want two static functions, and this will be a shader, and it will be called getShader. And it will just take in a string resource name is what we will say. And then we will have another function, public static. Actually, we don't even need this function. So what we will do is we will just check and see if we have a shader of that name. If we don't, we will just add it to our asset pool, and then we'll return that reference. So what we will do is we'll say file equals a new file resource name. So this is going to assume it's coming in as a file path. If you want to get real fancy, you could make individual folders. We do already. So you could like have it so that when they want a shader, you append assets/shaders, and then they just have to pass in the shader name. I have found that starts to get confusing because you forget that you do that, and then you start passing in full paths and everything. So better to just leave it as a resource name, but that's up to you. So we will be assuming they're passing in the full file path relative to the root of our project. Then we will say if shaders.contains key, and we are going to pass it in the file.getAbsolute path. So we want to pass in the absolute path, that way there's no confusion about like what the path is. We don't have random relative paths everywhere. Then we will say, let's just return it. We'll say return shaders.get file.getAbsolute path. And that should be good. Else, if we do not have it, we want to create a new shader. So let's say shader equals a new shader, and we will pass it the resource name, which should be the relative path. Then we will compile it so that we do not have to remember to do this anymore. Say shader.compile, and then we will say asset pool.shaders.put, and we will say file.getAbsolute path. And the shader reference that we just made, remember, this is storing a reference. This isn't storing the actual object, which is nice because that's just one byte, ideally. Then we will say return the shader. Nice and simple, right? So we just put it into this hash map. If we do not have it, we just create it on the fly and then put it in there. Typically in your initialization function, you would want to call this a bunch of times with all the different resources. That way you load everything. Like if you had a loading screen or something, you would be doing it in the init function of your scene. That way the player doesn't get lag spikes when it tries to get a shader that has not been loaded already. So we'll take a look at that too in a minute. We'll go into our init function and sort of do all this stuff too. Next thing that we can do, since we do have textures as well, why don't we make a getTexture function. So say public static texture, because a texture is another big one. getTexture. And this will also take in a string, which is a resource name. And I'm going to import this one as well. Let's go up here too, and we'll create a private static map from a string to textures. And this will be called our textures. And this is a new hash map. Now inside of here, we will do something almost exactly the same. We'll just say file equals a new file with the resource name. And then we're going to say if we have the texture. So we'll say if textures.contains key, resource name, or actually file.getAbsolute path. And then we will return asset pool.textures.get file.getAbsolute path. And let's actually make this a little bit more explicit. We will say asset pool dot for every single one of these, just so that that is completely explicit. And right up here too. Then we'll say otherwise if we don't, let's create one real quick and then return. We'll say else texture equals a new texture, and you can see it takes in the file path, which in this case is just the resource name. And then we will say just create a new texture, and then let's add it to our texture map. So textures.add.put file.getAbsolute path, and then we will put in the texture there. Then we will say return that texture. All right, so this should work perfectly fine now. Let's try it out and start removing some of those references that we had and turning them into actual resources that we only ever have one reference. So first, let's go into our scene, actually our level editor scene. inside of our init function. So instead of, well, actually, yeah, we'll do this. And then what we're going to say is down at the bottom of our init saying, we're going to say init resources, or we could call this load resources, right? And so this function is where we're going to put all those gets so that we just have a way to load all of our resources at the loading time. That way, when we go to get them, we are making sure we don't have to actually create them too. And if you wanted to, what you could do is inside of our asset pool, to make sure that this never happens, is you could make it so that get texture just returns it, and if it doesn't have it, then you could throw an error or an assertion here. That way you make sure that by the time you ship the game, you will not have any of these problems. So back into level editor scene, inside of load resources, what we're going to do is we're going to say asset pool dot get shader, and we're going to call this assets slash shaders slash default.glsl. So this will make sure we create that shader. Then, and it's also going to compile it here too. And we were using this inside of our render batch up here. And notice how we were creating a new shader per render batch. So what this was actually doing is we can actually say system.out.println creating new render batch. Because remember, we were creating 10,000 quads, each with a max batch size of 1,000 quads. So what we should see is that this will actually print out 10 times. If we run this, and then we'll take a look at our print. And sure enough, we get creating a new render batch 10 times. So what that means was we were creating 10 completely different shaders in totally different memory spaces for absolutely no reason. There's no reason to do that, right? Because the shader is the same. We shouldn't be doing that. So instead of doing this, now we can say asset pool.get shader, and we will say this is the assets slash shaders slash default.glsl. And now if we run this one more time, we'll see that it still works the same, but our reference count has now gone from 10 different shaders to just one shader that we are all referencing the same. So this is where the immediate feedback of this will start to come into play, is with your shaders and with your textures. In this tutorial, what we're going to be doing is texture batching. So as you remember from a couple episodes ago, we started our batched render, and that may have been a bit quick. So I'm going to go over it in a little bit more detail in this episode. And then we're also going to add one more feature, which is batching together textures, which is super important in games because, as you know, in 2D games especially, which is what we're building a game engine for, you typically have several different pictures that you want to display for different character animations, for different blocks, for different tile sets. And so this can be achieved pretty great with batching using batching textures. So we'll take a look at how all that works today, and we will code it and see if we can get it done. Before we start, like always, I do want to draw it and sort of explain what we're going to be doing. And before we even start explaining texture batching, I do just want to quickly go over what exactly batching in general is. So remember, we eventually want to have a game scene that looks like this. And we want to be able to, instead of drawing one sprite per draw call, which is what we would do if we created this as a game object and attached it, and we said draw, and then we just drew it sort of like we did in the first drawing the first square episode. And then we just drew this square, and then we did that for every single square. It would be extremely slow, which we also saw because when we limited our batch render to one draw call per object, it ended up going extremely slow at like 1 FPS. So what we want to do instead is just simply say, okay, let's batch all of these together. So we calculate the vertices in world space for every single object, and then we just stuff all of these vertices into one big array, and we just keep going for every single object until we get up to 1,000 of these squares, right? And we stuff that all into one big array, and then we can just say, okay, now draw all of these vertices at once. Now, remember, there is one more thing that we have to worry about, and that is every vertex has several different attributes, right? And we define those attributes. So what we were saying is, okay, we have an X, Y, and then the next part of the vertex is the color, R, G, B, A, And I think that was all we left it at. And so remember, for each vertex, we have to specify the X and the Y position. Then we have to specify the color we want that vertex to be. Then we move on to the next vertex and we start specifying that inside of our big float array. And then the last thing we have to remember is for every single sprite, there are 4 of these vertices. So we will end up doing 4 of these for one sprite. Hopefully that kind of visually shows you what we're doing. In terms of texture batching, that's sort of the next step for us because now we want to enable textures with our game. Now, you know that in most games, you are allowed to use a sprite sheet, right? Not allowed to use, but you just use sprite sheets because that's one way to do texture batching. And all a sprite sheet is, I'll pull up an example real quick. So right here we have a sprite sheet, and as you can see, it's just a bunch of different images all packed into one big image. And so then what we can do is we can just say with the texture coordinates, specify from here to here, and then from here to here, and sample only that part of the texture. So that's one way to do texture batching. But what if you have multiple sprite sheets also? Because in our particular case, we have a sprite sheet for the blocks, and we have a separate sprite sheet for some items and stuff. So now what you would have to do is you would have to start batching these together and say, oh, well, I can only do the blocks in this one. I can't really put Mario included into this sprite sheet because he's on a different sprite sheet. But no, we don't have to do that. And that's because modern GPUs, OpenGL specifies that all GPUs have to support at least 16 textures to be bound at the slot for any given shader call. So what that means is we can have up to 16 different sprite sheets bound to our GPU before we do a texture call or a shader or draw call. And then we can sample from any one of these 16 textures. So this is what we're going to do. And you can find out exactly how many textures you have using a function. I can't remember the name of it, but GL gives it to you so that you can find out because some GPUs support up to 32, some GPUs support up to 64, and you can query the computer to figure out exactly how many textures you can bind in one draw call. So what we're going to do is we're going to say, okay, we want to be able to bind multiple textures, and then we basically just want to store them in an array, and then we want to sample from the correct texture. And so all we will do is we will say, hey, which ID do we want the 0th texture, the first texture, the second texture, and then we'll use that to index into the array, which will give us the appropriate texture. So we could say, hey, Mario is in texture 1, the blocks are in texture 0. So when we're doing Mario, we're sampling from texture 1 in this array and 0 from these ones. But what if you want to draw just a color? What if you just want a square that has a simple color? You don't want a texture associated with it. Well, we can just reserve texture slot 0 as a special slot, which basically means if they have texture slot 0 as their ID, then we don't actually want to bind a texture. And so then that's what we'll do. And then we'll just use 1 as the first texture, 2 as the second, 3 as the third, so on and so forth, and then index into this array. Now, you may want a quick refresher on like texture coordinates and everything, which we talked about in the texture specific video in this series. So basically we just have the 4 texture coordinates, 0, 0 is the left, bottom left, this is 1, 0, this is 1, 1, and this is 0, 1. These are our texture coordinates. We use this to sample, and this is the same thing we will be doing in this tutorial. So we will need texture coordinates and we will need a texture ID in order to batch our textures. And so since we have this texture coordinates and these texture IDs, how do we get it into our batch? Well, remember when we wanted a color, we just include it as part of the vertex, right? This is our vertex specification. Well, how about we do the same thing and we include our texture coordinates. So we say UV0, UV1, and our texture ID inside the vertex as well. So we'll just expand our vertex attributes and say, okay, we're going to have the UV0 and UV1 here, and then we're going to have our texture ID embedded into these texture coordinates. And so that's how we will end up batching together our textures into this as well. So we'll enable a couple more attributes, and then we can start to use those attributes inside of our shaders, and then we can bind everything and make sure it all works properly. So let's actually start coding it and see if we can figure out how all this works in code, because I think that sometimes clears some stuff up a bit. Hey guys, this is Gabe from the future. So I actually finished recording this tutorial, but I forgot to include in the tutorial a fix that was found by one of the viewers. So something broke in one of the Java builds, and you may be experiencing super low frame rates for some reason. It's not because you're actually experiencing low frame rates. It's just because our time is messed up. So this thing does not work anymore. So what I'm going to say is delete this real quick because it doesn't work anymore. Don't know why. I don't know what happened, but it's in all Java builds too, because I'm on Java 8 and he was on Java 14 and it was broken in both. So it might be a Windows update that caused this. But anyways, instead of using time.time, just switch all of your time.time calls that were in here to GLFW, get time, and cast it to a float. And then there's one more down here, and just change that. It used to look like this, but you're just changing it to this. And that should fix any laggy issues that you had where you were getting super low frame rates for some reason. So just do that fix real quick, and now we can continue with this tutorial. Just to bring us back up to speed on the last tutorial, remember what we got to was this whole thing where we basically are just rendering a bunch of stuff. And actually in the last video, what we were doing was just resource management. So we'll actually make use of that too today with our textures. But what I want to do now is actually start this texture batching. So remember I said we're going to need texture coordinates and a texture ID. Well, what's the best place to store this stuff? For now, I'm going to say the best place to store this stuff is inside the sprite render. We may change this in the future. But basically what we can do is we can just say, okay, we're going to store a list of vector2fs. This could be our text chords. Because remember, we want a list that basically looks like, okay, first texture coordinate is this, second texture coordinate is this, third would be like this, and then fourth would be like this. Remember, we just have 4 different texture coordinates for the bottom left, or actually this would be bottom right, bottom left, top right, top left, respectively. And this is what we're going to store inside of these text chords. Then what we also need is we want a reference to a texture. So what texture is this guy referencing? Well, we can store that inside of our sprite render as well. Then what we can do up here is we can say, okay, well, if they want to create a sprite render with a texture, they can just pass in a texture instead. And then we'll say this dot texture equals texture. We'll say this dot color equals new vector for F1111. So we're going to make it white, and you'll see why in a little bit. Right here, we'll just explicitly set this texture to null so that we know for sure that that is null. Then we're going to go down here and we're going to say public texture get texture so that we can actually get a hold of this texture, and we'll just say return this dot texture, which will return null if there is no texture associated with this. I will say public vector2f get text chords, and we will just say vector2f array text chords equals a new, or actually we can just initialize it like this. And then we can say new vector2f in here, and I'm just going to do 1, 1, then new vector2f, and we can fix this in a minute too, because this definitely won't be right. And then another new vector2f, 0, 1, and lastly 0, 0. And then we'll just return those text chords. So we're going to generate them every time, which is a little bit of a waste. In the future, we will store them so that we can just return, like they'll be stored up here. But this is simple enough for our purposes. We just create 4 on the fly and then return it when they ask for whatever texture coordinates we are using. Okay, so now we have a way to get a hold of a texture and texture coordinates inside of this sprite render, right? Well, now we want to be able to send that data to our render batches. So remember, when we are adding sprites into our render batches, we basically can get all the information off of our sprite render from here. So the first thing that I want to do though is we changed our vertex specification, right? So now we have a position, we have a color, and then we have text chords, which is just float, comma float, and then we also have a text ID, which is just a float is what we will call it. So let's go down here and we're going to say, okay, so private final int text chords size is 2 because we only have 2 of those texture coordinates. And then we will say private final int text ID size is 1 because there's just one float for that guy. Then we will create the offsets. So we'll say private final int text chords offset is equal to the color offset plus the color size times float dot bytes. And remember, we're doing this basically, we're just saying where is this offset within the vertex? Well, it's offset from the colors offset, which is here, plus whatever the color size is, which will get us to here. And we just do it like this so that it automatically generates, and if we change anything, we don't have to worry about fixing that. Then we'll make private final int text ID offset, which is the text chords offset plus the text chord size times the float.bytes. And that will give us our text ID offset as well. And also the size of our vertex has changed. How many floats do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9 now. So we should change this to 9 because we have 9 floats inside of one vertex. Okay, and then mostly everything else should remain the same, but since we added those attributes, we also have to add the attributes down here and tell it, hey, we have 2 new attributes that will be coming in. So say GL vertex attribute pointer 2, which is going to be not our color, but our text chords size. And then this is going to be a float, not normalized. We're going to say vertex size in bytes because we need to give it that. And it's just going to be text chords offset is the offset. Then I'm just going to copy this and move it down here because we just need that. And I'm going to actually copy both of these and just move them down here. And then we want to say, so we also want to enable a third attribute, and this is going to be our text ID. So we'll say text ID size, and we will move down here and say this is the text ID's offset. And everything else should remain the same. So now we have our attributes enabled so that the GPU knows we added these 2 new attributes to our our vertex. So now we should be able to use them once we actually get into the GPU, right? Now, when we actually add the sprite, we have to load these properties in. So remember when we go down to load vertex properties, we're loading 4 vertices per sprite because one sprite has 4 vertices. It's a square. And so we want to load the position and the color because that's how our vertex goes. But now we added 2 new attributes. So we also want to load the texture coordinates and we want to load the texture ID. And we will store these just in increasing order respectively. And then let's go up here and actually get a hold of those, right? So what we're going to say is int text ID equals 0. So we'll initialize it to 0, say we don't have a texture yet. Then what we can say is for, actually, this brings me to my next point. How do we know what texture they're using if we have a list of textures? Well, we don't even have a list of textures. Remember, we want to be able to support multiple textures inside of this batch. So what we should do is say we have a private list of textures, and this will be the textures that are contained within this batch. So whatever textures we have available to use in this batch, right? Inside here, we'll just initialize it to a new array list. And then we now have that texture, but it's currently empty, right? We want to actually add it if we get some textures that we want to be in here. So what we can do is we can say, okay, right before we load this sprite, if the sprite.getTexture does not equal null, so the sprite has a texture, we want to use that texture, then we want to check, do we already have this texture? Have we already had it added by some other texture, some other sprite? So say now, if not textures dot contains this sprite's texture. So if we don't already have it, then we want to add it. So we'll say textures.add sprite.getTexture. And all this does is we're basically saying, okay, does this sprite have a texture? If it does have the texture, and if we don't already have this texture inside of our list, let's add it to our list of textures. That way we can use it in the future. Now that we have this list of textures that should be getting the sprite's textures added to it as they get added, we can load it down here. We can say for int I equals 0 until I is less than textures.size I++. And then basically we can say, actually, let's only do this if the sprite we're trying to add has a texture. So if sprite.getTexture does not equal null, then we will start doing this for loop because otherwise we don't even have to worry about it. Then we'll say if the textures.get I equals sprite.getTexture. So if we are on the texture that our sprite has, then that is the text ID we want to use. And then we'll break out. So basically what we're doing now is we're just saying find the texture ID that we want to use, and if we hit it inside of our textures, we're just going to map it directly. So basically we'll have a list of textures. We'll have like text, 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 a bunch of textures, and we will loop through until we find the one that matches our sprite that we're adding right now. And then we'll say the text ID is just the ID in this array because we're going to upload it 1 to 1. So this would be the first texture, second texture, third texture, and we'll just map it directly. So that's our text ID. Now we can go down here and we can say vertices offset plus 6. It's going to be something different equals text ID. Let's actually copy this real quick. We have 2 texture coordinates, right? So this will be 6 and this will be 7, and then this will actually be 8. There we go. And these are not going to be color.w. This could be the text ID, whatever, or the text chord ID, text chords. So let's get a hold of those texture coordinates too. We can just say vertex vector2f text chords equals sprite.get text chords. And that should get us our texture coordinates that we just hard coded in for now. And then down here, instead of doing color, we'll say text chords i.x and text chords i.y. And we can do I because remember we're looping through for every vertex 0 through 4, and so then that will loop through the texture coordinates which we just defined inside the sprite render 0 through 4, and then we can just get the x and the y and stuff it into our array so that it has the appropriate vertex. All right, so now we should have all of the data being sent to the GPU as well. We have one more problem though. We're not binding any textures. Remember in the texture video, we had to bind the texture before we actually started to draw elements so the GPU knows what's happening. Well, we have that same exact problem now. We need to bind that texture before we can draw it. Well, we have several textures to bind, don't we? Yeah. Well, OpenGL gives us these texture slots. We can bind multiple textures. So what we want to do is bind every single texture we have. So we'll say for int I equals 0 until I is less than texture.size, I plus plus, and then what we want to do is we want to say, okay, let's activate the correct texture slot that we're going to be using, which is GL texture 0 plus I. So this is slot 0, and then when we add I, it will give us, if I is 1, slot 2, slot 3, as I increases. So we'll activate the texture in the appropriate slot. Then we'll say textures.getI.bind. So now we're binding whatever texture we have at index I to whatever slot is at index I. So we're getting that 1-to-1 ratio that I just talked about. And last thing we need to do is we need to upload an int array, which we can't do right now, but we'll create this function in just a second. And this is going to be called uTextures, and this is going to be our texture slots. So basically this is going to tell OpenGL, hey, these are all the texture slots that we are uploading. It's sort of like uploading a texture. Remember, if we go into the shader class, when we upload a texture, all we're doing is we're really uploading one integer. So if we want to upload multiple textures, what we're going to do is we're going to upload a int array, take the variable name, and we're going to take an int array. And we'll just copy all this because it's mostly the same. And instead of doing uniform1i, we'll say uniform1iv, and it's going to take the array. And all the v means is value, which basically means this is a value pointer. So it can take in just an array. It's weird. It's a little bit C++ under the hood, so that's why it looks like this. But now we're uploading an entire array of ints. So just like we uploaded one texture, multiple textures, because it's an array. Now let's go back to our render batch. We actually need this array of texture slots, which we can define at the top. We'll just say private int text slot equals, and we'll just say 0, 1, 2, 3, 4, 5, 6, 7. We literally just want to go from 0 to 7 because it's just going to be indexing into this array that is 0 to 7, which will index into the appropriate texture. It's kind of weird, I know, but we will take a look at it in the shader and sort of see what's going on there too. So we upload an int array, which is just 0 through 7, which correlates directly to these textures that are being bound at slots 0 through 7. Then what we can do is we also want to make sure that we unbind all of our textures before we leave. So we'll just say copy that loop and then textures.getI.unbind, just to make sure that we don't have any of them bound for the next draw call, so we won't get any weird bugs. And this should be it. We should now be able to use textures Let's go into our shader though and modify it, because now we're using this new uniform and we have a couple new layout locations, right? So remember, we enabled a couple more attributes. So we have to say layout location equals 2 is a vec2, and this is a text chord. And then we're going to say layout location equals 3 is a float, and this is going to be a text ID. And if we go back into our render batch, you can see this directly right here. So remember, 2 text chords, 3 text ID, default.glsl, 2 text chords, 3 text ID. So that's where this information is coming from, these 0 through 3 and everything. So now we just want to pass those to our fragment shader. So our fragment shader will say, okay, I also want the text chords, and I also want the text ID. And we will gladly pass that to our shader. So we'll say out vec2 f text chords and out vec float f text ID. And then right down here, we will just pass it along. We'll say f text chords equals a text chords, f text ID equals a text ID. And then inside of our fragment shader, once again, we are also taking a uniform, which is an array of textures. So we'll say uniform sampler 2D U textures is an array with maximum size of 8 is what I'm going to say, because we should never need more than that. You could do 16 because OpenGL specifies you need at least 16. You could do 64. You could do whatever you want. I would highly recommend just keeping it low. That way lower end devices don't have to worry about running out of texture slots. So we create an array of sampler 2Ds, which is our textures, U textures. And then we can just say our color is F color times texture. And then we're going to give it U textures, F text ID, and F text chords. So we're sampling using F text chords from the texture located at this ID. But there's a problem. If we try to do this right now, F text ID is a float. We can't index into an array with a float. So we should say ID equals int. We're just going to cast it to an integer. So we'll say ID equals integer F text ID, and then we'll just pass in ID there instead. And remember, we initialized F color to white, which is 1, 1, 1, 1. Well, what happens if you multiply 1 by some other color? So it looks like this times some other vector. What would happen is this would multiply by this will multiply by this by this, and this by this. And what ends up happening is this equals the exact same thing we have right here. And we just get the color that we wanted. So this will give us the appropriate color no matter what, as long as F color is white. But this also gives us the ability to tint our sprites, which we can take a look at too in the future. Let's run this real quick and just see what happens. Okay, so we get black. And that's because if we go into our test scene or our level editor scene, remember, we are just uploading sprite renders without texture. And remember, we said we want to reserve texture slot 0 to be the empty texture, just the color, right? But we're not really doing that, right? Because we're saying text ID is 0, and then we're looping from 0 to textures.size and just assigning that here. What we should do is, instead of assigning it to I plus 1, that way, if we have text in our array, what we're actually going to end up with is a 0 here. And this 0 is our special reserve slot that does not hold a texture, but instead is just to let us know, hey, we just want to use the color here. So instead we'll say I plus 1, and if there is no texture, if texture is null, then we'll use text ID 0, which should work just fine. And then up here, instead of binding texture 0 plus I, we want to do plus 1 here too. That way we end up getting the appropriate texture slot. Then let's go back into our default.glsl, and we'll say if f text ID is greater than 0, then we are using a texture. Otherwise, we're just using the color. So we won't even worry about that. And if we run this again, we get our colors back, which is great. Now we want to see if we can actually bind to textures, right? So I have 2 test images right here. They're super small right now, but basically just Mario and a Goomba. I will be using those to test them. They're named testimage and testimage2.png respectively, and they're located in my assets/images folder. You can download them if you want. Let's go into our scene. So back into our level editor scene, and I'm gonna get rid of this guy, and we'll actually just go all the way up here. Get rid of all that, and then we'll say game object obj1 equals a new game object, and we're just gonna call this object1. Give this guy a new transform. We'll say 100, 100. Actually, transform, new vector 2f, 100, 100. This is the position. And then for the scale, I'm going to say we'll do 256 by 256, which should be like the pixel size of our projection. And then close that off. Then we'll say obj1.add component, a new sprite render, and we want a texture, right? So we can say asset pool.get texture, which will load it automatically for us, assets/images/testimage.png, and that's actually testimage1. Go over here. So we've got that semicolon. We're good. And then we will say this.add game object to scene obj1. And I'm just going to do the same thing. Copy this, except this is obj2. We're going to call that 2. And I'm going to move him to like 400 so that he's not in the way of the other texture. And then we're going to add 2 here and here. And then instead of testimage1, it's testimage2 now. So now we should have 2 different textures. But what's going to happen? Let's see what happens. Oh, we get an error. Oh, because I named my images wrong. It's testimage and testimage2. So let me take away that 1. Run this one more time. Okay, so we get it. But as you can see, they do not look right at all. What the heck is going on here? Well, this is a UV error, right? Our UV coordinates are not correct. Remember, this should be 0, 0, 0. This should be 1, 0, 1, 1, and 0, 1. Let's check and see what our texture coordinates actually are. So let's go into our shader. And instead of doing color equals this, I'm going to comment that out. I'm going to say color equals vec4 ftext chords 0, 1. And so what this is going to do is it's basically going to make a color that is our text chord X and Y, and then 0, 1. So RGBA. So basically we want 0, 0 should be black, 0, 1 would be green, 1, 1 would be yellow, and then 1, 0 would be red. So we want black to be in the lower left corner. It's in the top left. We want green to be in the lower right corner. We want red to be up here. Yellow is in the right place, but we need to swap these two. Swap these two and this. So first, let's get black into the bottom left. That's 0, 0. We need to swap that with this guy, which is 0, 1. So let's go into our sprite render. And let's swap 0, 0 with 0, 1. So we'll make this 0, 0. And we will make this 0, 1. This is inside sprite render. We run this again. We have swapped those now. Now we need to swap these two because these are in the wrong place too. So this is 0, 1. This is 1, 0. Let's swap those. So we will say this should be 1, 0. And this should be 0, 1. And now if we run this one more time, okay, there we go. Now we have it in the correct order. So let's run this one more time. Let's change our sprite shader to actually output the color of the texture. There we go. We get it again, but they are sideways. So I clearly messed up my texture coordinates. Again, I actually don't think we were supposed to swap those last two. Okay, yeah, so ignore my advice on that last one. I was just doing the colors wrong. So this should be 1, 0. This should be 0, 1. That was correct. But we still have a problem. They're upside down. Why are they upside down? Well, that's because OpenGL sort of does things a little bit backwards. And there is one easy way to fix this. Remember, we had this problem too in our texture specific video. What we can do is we can just tell STBI to load our image upside down, which will correct this. So we'll say STBI set flip vertically on load to true, which will flip it vertically. And now we get our sprites in the correct order. So this is now all functioning correctly, and we can load up to 2 textures. We are running out of time, but there is one more thing that we need to do. I will leave this as an exercise, and then we will cover it in the next tutorial. So in our render batch, we are just adding textures if we do not have them. So if we go into when we add a sprite, we just check and see if we have the texture inside of our array or our list. If we don't, we add it. What happens if we add more than 8 textures? We add a 9th. That should not happen. We don't want to do that. We want to limit it so that if our batch fills up with textures, it should stop and then it should move on to a new batch and start a new batch that has the texture that you need. We will cover this in the next tutorial. This will all be going on in the render. It's not too bad. Give it a try if you want. Basically, if this has no more room for textures, then we should move on to a new batch. That's the gist of what we want to do. But this has been texture batching. I hope you guys enjoyed this. If anything didn't make sense at all, please leave a comment and I will try and clear that up. It's just a kind of difficult concept to wrap your mind around and stuff. But I hope the visual explanation helped a little bit, and I hope that this is starting to make a little bit more sense. It will come with time, I promise. It just takes a little bit. So in the last series, what we did was we got texture batching working. We did not complete it though. We still have to fix one issue, which we will do at the beginning of this episode. But then after we fix that, we will start working on Spritesheets so that we can have one texture with multiple sprites on it that we can sample specific sprites from. So the approach we're going to take is a pretty basic one, but it will work, and that's all that matters. So let's take a look at how we will be doing the Spritesheets, and then we will actually code them. Like I said, before we actually code this, I do want to talk a bit about what Spritesheets are. I'm sure you all already know what a Spritesheet is. It's just a bunch of sprites jumbled into one texture. Think of like Minecraft's block palette too. All those jumbled in one texture, that's a Spritesheet. And so we can use these to our advantage because we can put multiple sprites into one texture, which is really nice. Now, how do we actually take advantage of this though? Well, remember how I said that in textures, this top left corner is actually 0, 1, this bottom left corner is 0, 0, the very bottom right is 1, 0, and the very top right is 1, 1. That means that every value in between is something between 0 and 1. So if we want to find out what the texture coordinates for this specific Mario sprite is, so we have him right here, I know for a fact that these sprites are all 16 by 16 because I set up the assets. So I didn't make them, but I did set them up so that they would be all the perfect size. So how would we find out what its texture coordinates are? Well, we know that this bottom left coordinate is going to be 0x, but then it's going to be 16 for y because it's 16 pixels up. This is in pixel values, right? And 0 is the 0 is the bottom left always for OpenGL. So we have to remember that. Now the top left would be 0, 32. Then the top right would be 16, 32. And then the bottom left would be 16, 16. So this is our values in pixel values, which we can get pretty easily. If we know the width of each sprite, and if there is like 1 or 2 pixel spaces between the up and the down, we can calculate this pretty easily. We just literally loop through. This would be 0, 0, then 0, 16, then 0, 32, so on and so forth, until you get all of them. I think I had that backwards, but whatever. And then you would do the same. You would, once you reach the end, you just bring your x back to 0 and then start looping through again. And then you go back to 0 and then you start looping through again, and then you can get the coordinates for every single sprite. But our next step is to convert these to normalized range between 0 and 1. How do you do that? It's really easy. You just do 0 over the total sprite's width, the total texture, so this whole thing's width. And then you would do 16 over the whole thing's height. And then you would do a 0 over the whole thing's width, and 32 over the whole thing's height. And so on and so forth. And what that's going to do is it's going to normalize these pixel values so that they are in a value between 0 and 1. And then we can use these as our texture coordinates. And we can subsample, we can sample specific portions of our texture and send that to our GPU just by sending different texture coordinates, and then it will sample from wherever we pass these texture coordinates in. So what we are going to do is basically, when we have a sprite sheet, we are going to say, okay, how many sprites do you have? Well, this has 26. What's each sprite's width? Well, it's 16. The sprite's height, 16. And then we can get the image data. So the texture contains the overall width and height of the texture. Then we can literally just say, okay, and then do you have any spacing? In this case, no, there's no horizontal spacing or vertical spacing. If there was, then we would say, oh, there's like 2 pixels for horizontal and 2 pixels for vertical. And you could have those be separate. I typically leave it the same because it's just easier. But yeah, and then we can use this data to just loop through and create a list of sprites that have each of these texture coordinates specifically for each sprite. And then we can say, okay, I want the 0th sprite, which we could call him or we could call him. I'm going to call it the top left corner. Then this will be the 1st sprite, 2nd sprite, 3rd sprite, 4th sprite, 5th, so on and so forth. And then this is how we can retrieve sprites. We no longer have to think about texture coordinates. We just ask for sprite 0 and it will look up whatever sprite 0 is and then give you the appropriate texture coordinates and everything. So this is the approach we're going to take. It's going to make a little bit more sense in code, I think. So let's actually code this out and see how it works. Before we start coding the sprite sheets, let's go into our render and fix that one problem we had. Remember how I said that if we actually go over the amount of textures we have, right, we just keep adding textures? That's not good. We should have a limit. So inside of our render batch, what we're going to say is public boolean has texture room, which will tell us whether we have room for more textures. And this will literally just return the size of the textures is less than 8. And we want to return this. So we will say if we have less than 8 textures and then we still have some room, then we will say public boolean has texture. So we can check and see if we have a specific texture, and then we'll say text. And we'll just say return this .textures .contains that texture. And with these 2 methods, we can now make sure that we limit it when we are adding in sprites. So then up here inside of our render, when we go to add a sprite, as we're looping through, we're not only going to check if the batch has room, but then we're going to say sprite, actually texture, text equals sprite.getTexture. If text does not equal null, and this batch has the texture, or this batch has texture room, and then we can add it. And this should be grouped together because this is one logical grouping. So what we're saying is if this sprite has a texture and this batch has the texture, we can add it. Or if this sprite has a texture and the batch has some texture room, then we can add it. And there is one last or. What if the texture is null? Well, then we don't care. If the texture is null. So if the texture is null, then we don't care, we can add it regardless. And let's hit simplify and see what IntelliJ does for us. So I guess this logical if statement can actually be reduced to just if the texture is null, or we have the texture, or we have texture room. And that is equivalent. So I'm going to trust IntelliJ on that one. But basically all we're saying is if we can add this sprite to this batch, then we will add it. Otherwise, we will not. And we just check for textures. If we run it, we'll get the same exact output that we were getting last time, and you see that that is all working correctly. So now let's move on to sprite sheets. So in order to have a sprite sheet, we actually need the concept of a sprite. Right now we have the texture coordinates and the texture stored inside of the sprite render. Let's offload this so that they are actually stored inside of something called a sprite, which the sprite render has access to. So we're going to create a new class, call him sprite. And then we're going to say you can create a sprite using a texture. And we'll import that. And this sprite is going to have a texture. And this sprite is going to have texture coordinates, so text coords. Then we will say if you initialize it with a texture, we'll just say this .texture equals the texture. And what are our texture coordinates? Well, we're assuming if they just pass in the texture, they want it to be the whole image. So we'll just give it the default text coords, which are these. So then we'll say, and text coords, this .text coords equals those texture coordinates. Then we will have one more method, public sprite texture, and a vector2f array text coords. So then we will say, okay, if you know what the texture coordinates are, then you can pass them in when you're creating it, and we will just initialize it here. And so then we will just set it to whatever texture coordinates are passed in. Then we'll provide a couple of getters. So we'll just say public texture get texture, return this .texture. and we'll say public vector 2f text chords, and we will say, whoops, return this dot text chords. So this should offload everything. Then inside of our sprite render, instead of doing this, what we're going to say is return our sprite dot get text chords. And instead of saying return this dot texture, we'll say return sprite dot get texture, which should be good. Then up here, instead of initializing it with a texture right here, we'll say initialize this with a sprite. And instead of saying this dot texture equals texture, we'll say this dot sprite equals sprite. We will get rid of these two references because we no longer need them. And then instead of saying this dot texture is null, if we just want a color, we will say this dot sprite equals a new sprite. And for the texture, we will just pass in null, which we know will give it an old texture here, and then it will give it the default texture coordinates, which should give us feature parity to what we had just a moment ago. So if we run this, we should get the same thing, except it's going to say we are passing in a texture. So instead of doing this, we can just wrap this in new sprite, and we can wrap this one in new sprite, and it should work exactly the same. So if we run this one more time, we get the same image. Okay, so we didn't really change anything here, right? We just moved those into the sprite, and then we just said, okay, instead of the sprite render holding those specifically, it just holds a sprite and then returns the texture coordinates and texture from the sprite. What's this going to do for us? Well, this is going to make it so we can be a little bit more flexible with our sprite chords and stuff like that. So let's use that flexibility now by creating another new class, and we're going to call this the sprite sheet. Now, what is the sprite sheet going to hold? Well, this is going to hold a texture, and this is going to be its texture. So this could be like the parent texture, the overall image, like I showed you in the drawing. Then it's also going to have a list of sprites, and this is going to be its sprites. Then when you're creating a sprite sheet, we're going to pass in all that information I said. You're going to want to know the texture that you are coming from. We're going to want to know how big is each sprite, the sprite width. We're going to want to know how big is each sprite's height. And then we are also going to want to know how many spaces, if you have spacing. Let's actually do number sprites first and then int spacing. So how many sprites are in this, and then what is the spacing? Do you have any spacing? And we will pass all that into the sprite sheet. Now, right now, our textures don't actually hold how big they are. We do get it because we get the width and the height here, but we're not holding it inside the texture. So up here, I'm going to say private int width and height, and we are going to store these. So if the image is not null, then we're going to say this dot width equals width dot get 0, and this dot height equals height dot get 0, which means we got the width and the height already when we loaded the image here. So now we're just storing the width and the height so that we can later get it if we want to. So we'll just return this dot width, and we'll say public int get height, return this dot height. Now let's go back into our sprite sheet. So now we have a way to get the overall width and the overall height, and we have the texture, we have the sprite width, the sprite height, number sprites, and the spacing. So we have everything we need to create this list. So let's say this dot sprites equals a new array list. We will initialize it to empty. So this dot texture equals the texture passed in. Then we're going to say int current x equals 0. So we're starting at 0, and we're going to start at the top of the image because we want the top left to be our 0th sprite and so on and so forth till the bottom right would be our last sprite. So we'll say current y is actually texture.getHeight minus the sprite height, which will give us the bottom left corner of the top left sprite. Okay, just think of that image, and it's the top left sprite, bottom left corner. And then we're going to say for int I equals 0, until I is less than the number of sprites, I++, we're going to loop through until we get all the sprites, and we're going to calculate all of those coordinates. So we're going to say float top y equals something, float top right x equals something, float left x equals something, float bottom y equals something. And this is going to be our normalized device, or normalized sprite coordinates. So remember how I said, well, this current y is actually the bottom y, this current x is actually the left x. So we can get those ones pretty easily. So we'll say left x is actually our current x over casting to a float the texture.getWidth, because we just need to divide by the width to get this normalized. And same thing with the y, it's just the current y over, I cast it to a float, and then we'll say get height, because we need to make sure this is normalized. Then for the top right, or the top y and the right x, we just need to add the sprite width and the sprite height to these values to get those, right? So we'll just say, okay, well the top y is just the current y plus the sprite's height over, and then we'll say float texture.getHeight. And we're going to say the right x is current x plus the sprite width over the float texture.getWidth. And this will make sure that we have all of these in normalized device coordinates and that they are correct. So now let's create our texture coordinates using these. We'll say vector2f text coords equals, and we're going to say new vector2f. Actually, let's do this. We'll just copy from our sprite the normal. So this is what it normally is, and then we will copy these here. And we know that this is the right x, this is the top y, and so on and so forth. So we'll just replace the ones with right x and top y, and the zeros with left x and bottom y. So we can say that's right x, this is right x, this is bottom y, and then we can say this is bottom y, this is top y. We can say this is left x, and we can say this is left x. And then that should be the appropriate texture coordinates now. Then we'll just create a new sprite using this data. So we'll say sprite equals a new sprite. Pass in the texture, which is this dot texture. We pass in the texture coordinates, which is the texture coordinates we just created. Then we'll add it to our list. Then we will increment our current x and current y. So we'll say current x plus equals sprite width plus spacing. So we move it over so that we're onto the next sprite. And then if the current x is greater than or equal to the texture's width, then we know that we have reached the end of the texture. So we will move our current x back to 0. And then we will move our current y down a sprite so that we start moving down the texture. So we'll say sprite height plus the spacing. And then that should make sure that we move across the entire texture. Now, one last function that we will want, which will be nice, is public sprite get sprite, and this will take in an index, and then we'll just say return this dot sprites dot get index, which will just return whatever sprite the user asked for from this sprite sheet. Now, we want to add this to our asset pool because we only ever want one copy of our sprite sheets. So let's go into our utilities, into this asset pool, and we will create a couple methods. Because sprite sheets are so custom and we do need to create them ourselves, we're going to add a method to add a sprite sheet right here, where we will basically just take in a string, which is the resource name, and then we will take in a sprite sheet, which is the sprite sheet. Then we'll just say file equals a new file resource name, and if not, actually we need to create a list to hold this to, or a map. So we'll say private static map from a string to our sprite sheets. This is our sprite sheets equals a new hash map. And then we can use this down here. We'll just say if not asset pool dot sprite sheets dot contains key, the file dot get absolute path. So if we don't already have this, then we will just add it. So we'll say asset pool dot add sprite sheet, and it's the file dot get absolute path is what we're going to use, and we will add that sprite sheet. So then we can create a very similar method, public static sprite sheet get sprite sheet, and we will take in the resource name here, and I'm just going to copy all this because it's literally the same. Then the one different thing we're going to do from what we've usually done is if we do not have it, instead of creating it, we're going to say assert false error tried to access sprite sheet plus the resource name plus, and it has not been added to asset pool. So we'll just tell ourselves, hey, you just tried to get a sprite from a sprite sheet that's not actually in the asset pool. And that will return just nothing. So then we'll say return asset pool dot get, actually dot sprite sheets dot get or default. And then what we're going to do is we're going to say file dot get absolute path. and the default value is null. So this will just ensure that if we are in release mode and we hit this assertion for whatever reason, it's not actually going to do anything. This is all going to get removed. So then if we are in release mode, it will just return a null value instead. If you wanted to be really safe, you could probably have a default sprite sheet that just has no sprites and would return like empty sprites that way, or like a pink sprite like Minecraft, so that if for some reason a sprite sheet gets corrupted or something, then instead of your game crashing, what would happen is they would just get those pink images instead. We're not going to worry about that for now. That's for the future. But now that we have this functionality, let's actually try and use it. So let's go back into our level editor scene. And when we are loading resources, we will say asset pool.add sprite sheet. And I'm going to call this assets/images/spritesheet.png. I have that image located in my images folder now. Then I'm going to say this is a new sprite sheet. Actually, let's move to the new line. This is a new sprite sheet. And this takes in the texture. So we're going to say that's asset pool.get texture, assets/images/sprite-sheet.png. And then we need the sprite width, which is 16, sprite height 16, the number of sprites is 26, and the spacing is 0. Then this will add the sprite sheet to our resources. Let's move this to the top of our init method. That way we load resources first. And then I'm going to grab that sprite sheet. I'm going to say sprite sheet sprites equals asset pool.get sprite sheet. And this is assets/images/sprite-sheet.png. And now we can use this. So instead of saying this is a new sprite render, new sprite, all this stuff, we can just say this is a new sprite render and we are using sprites.getSprite0. And same thing down here. I'm just going to give it a random one, sprite.getSprite10. And so then this should get two different sprites located on the sprite sheet. And we're going to get an error. Oh, whoops. We called assetPool.add sprite sheet within add sprite sheet. This should not be happening. We should say assetPool.spritesheets.put. And then that should be good. Okay. Now if we run this, you notice we get two different sprites, which is pretty cool. And if we go into our level editor scene and we just change the index of this to 15, it instantly changes to a new sprite. And this is great because now instead of having to load individual images, we can just do this and then we can index into one sprite sheet very simply and get a much better variety pretty easily. So yeah, one thing you might think about trying to do is, oh, this is really cool. I'm going to try and inside of my update loop, just change the sprite on the object. And that way I get a little animation running. And that would normally work, but it's not going to in this case because we are not reloading this data every frame. And in order to do that, we need to add a dirty flag system to our batched render, which will probably be the topic of the next tutorial. So this batch render does take a bit to get it working properly, but once it does, it's super nice to have. So yeah, this was sprite sheets though. So in the last episode, what we did was we did sprite sheets. We gave us a way so that we can now get individual sprites off of a bigger sprite sheet that contains multiple sprites jumbled up into there. We can't really use that though. So a nice way to be able to use this is with animations. Now you can have animations because you have multiple sprites, but we have no way to tell the GPU that a sprite has changed. So in this tutorial, what we're going to be covering is something I call a dirty flag system. Basically, all this means is anytime one of the sprites or our game objects is changed, we tell the GPU, hey, something's changed, and then the GPU goes and redraws it and makes it better. So that is the goal of this tutorial. We will get that dirty flag system up and running, and then we will have a way to change our sprites and get some cool animations and stuff going. Let's talk about how this works in a little bit more detail, and then we will code this up. So before we begin coding, let's talk about what this whole dirty flag system thing that I came up with is and why we need it. Well, in order to understand that, we need to understand our game world, right? Our game world has a bunch of sprites, which, as we remember, are just squares with some picture in it, right? That's what our game world is made up of. Now, at any given moment, this sprite could be moving because of its game object, right? Its XY could be changing. We could be changing its color because who knows, maybe it hit something and you want to blink it on and off the alpha. It could be changing its UVs, right? Because all of a sudden its texture ID changed and we need a whole new UV. It could be changing its image completely, which means its ID is now in a completely different texture, which we need to think about, right? Because it's animating, it's changing its images. All these things are things that could be changing, but there is a problem, right? Where are we doing all of this? Where is this all happening? Well, that's happening on the CPU, right? Because our CPU is the one that's running the program, and it's the one that's doing the updates every frame and saying, hey, update all the game objects, and then when the game objects are updated, then all of a sudden the sprite changes because of something in the game object told it to change, blah, 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 blah. But who's doing the drawing? That's the GPU. The GPU is doing the drawing right now, but the CPU is changing a bunch of this data. That means the GPU should be drawing different things, but it doesn't even know that this stuff has changed because it's only being told by the CPU, right? So we need a way for our CPU to say, hey, GPU, we have changed a lot of stuff. Here's the new vertex buffer. Draw this one instead. And then basically the GPU is going to be like, okay, so I am going to draw new stuff now. So how do we do this? How do we keep track of stuff that has changed and stuff that has not changed? And the best way that I have found to do this is similar to how HTML documents update their systems. It's not really similar, but it's the same concept. They have a dirty flag system where if any element on the website has changed, and then they only update that portion, and that's what we're going to be doing. If any sprite in our game world has changed, then we only reload, say this one changed, we only reload his data. We don't care about him because he's the same. That way we have to reload minimal data, and it makes it a little bit better. Hopefully, I haven't done any performance testing, so I don't know how much this will actually speed things up and stuff. But this is the approach we'll take. And the way that we can accomplish this is by basically saying, hey, this sprite is dirty, which means we need to reload his data. So if the position, the color, the text chords, or the text ID, these are all things that are in our vertex data, which the GPU cares about. If any one of those changes, we need to say, hey, the sprite is dirty. Now, where should we do that? Should we do that on the game object? I would say no. The game object itself is just an entity. It doesn't care about how it's being rendered, right? This is all rendering stuff that we're having to deal with. Well, where else could we put it? Do we put some custom flag inside of a whole new component that basically just tells us whether a sprite's dirty? And I would argue no to that too. I think the best place to actually put this is inside of our sprite renderer, right? Because he currently has the position via the game object, the color, because he stores that internally, the texture coordinates, and the texture ID. All this stuff is already contained inside of here. So he should tell us when anything changes. And when something does change, then he should say, okay, I'm going to set this flag dirty to true. I am now dirty because something has changed. And this is just a Boolean variable. It's not an actual flag. Then inside of our render batch, when we are looping through all of our sprites, we can just say, well, we'll have to loop through all the sprites before we actually draw anything. And then we can say if that sprite's dirty, we'll then just reload his data. Then, if any of the sprites were dirty in this whole loop, then we need to rebuffer. So we'll send the data back to the GPU with a GL call. And doing it this way maintains this strict decoupling of the render batch and the sprite render, which is really nice. Notice this communication is happening implicitly rather than explicitly. The sprite render does not tell the render batch explicitly, hey, I need you to change because something has changed within me immediately as soon as this happens. And instead, it implicitly changes a flag about itself. This render batch knows it has to check for these things every frame. And so then it sees and loads it. And so this sort of implicit communication allows us to maintain, like I said, the strict decoupling, which is nice because the more dependencies, the more codependencies you have on your code, the harder it will be to change things in the future. Technically, this is a codependency too, but it's also not, because if we removed this whole dirty flag system completely, our render batch would still work. It would be fine. Nothing would have to change in here. Whereas if we had this calling some function on the render batch, and then all of a sudden we remove that function from the render batch, well, our whole code base is broken. So this is the reason we're doing it this way. Decoupling, it's nice. Okay, one last complication. You'll notice I have a question mark under text ID. Why do I have that question mark? Well, if you remember that text ID tells us what texture we are sampling from, right? Well, if you also remember, I said one texture batch can have up to 8 textures. So say we have 8 textures in batch 1. Say we have another batch, batch 2, that has 2 new textures. So we have 10 textures total that we are sampling from in our game. Say this text ID changes because it has changed textures. But say it was 0 and it changes to text ID 0, but it's actually 0 in a completely different batch. Well, what that means is that this sprite no longer even belongs in batch 1. It used to be in batch 1, but since it's changed textures to a texture that we don't even have in here, we have to completely remove it, then re-add it to batch 2. And that's beyond the scope of this tutorial because that involves deleting vertex properties and everything, which we aren't going to get into just yet. We will get into that in the future though. And when that comes up, we will handle this case where all of a sudden we have sprites moving from completely different batches. All right, now that we have a little bit of this down though, let's actually code it and see what we can get done. All right, so I'm back in the code. Let's go to the first little bit, which will be the easiest part, which is detecting if something has changed. So if we go back into our sprite render, which is actually up here, you'll notice that we have some of these properties as private, which is really good because that means if they change, we will know, right? So the only way that these could change is if somebody calls these new functions that we're about to say. So we'll say set sprite, and then this dot sprite equals that sprite. Then we should be good in terms of texture coords and texture because that data is coming from here too. Then we will have one public void set color, and then we're going to take in a vector for f color, and then we'll say this dot set color, or not this dot set color. We'll say this dot color dot set color, which will basically just copy the RGBA values directly into this vector. So now we have these, and that should be good. That's the only things that will really be changing is the sprite and the color. And then the last thing that's going to be changing, remember, the position. How do we tell if the position has changed? Well, the easiest way to do this is literally just to keep track of the transform. So we're just going to create a variable that says last transform, which basically means this is the last whole transform. So scale everything that was recorded for this sprite. If anything changes on this, we want to change the sprite. That way, if something like the scale properties change or something like that, we also get notified. So let's make this a little bit easier on our lives, and let's go into transform. And let's create a copy method real quick. So we will say public transform copy. This will return a copy of whatever transform this is. So it will say transform t equals new transform, and it's going to use new vector 2f this dot position and new vector 2f this dot scale. This, by passing in a vector to a new thing like this, it will just copy the contents into a completely new vector. That way we don't get any problems with different things. Okay, so then we'll just return t. So we make a copy of it and we return it. And it's going to tell us we can actually inline this, which is nice. Yeah, saves an instruction or two, which is cool. And then we will make one more function, which will make our lives easier too. We will say public void copy transform 2. So this one will copy the contents of this transform, so this to 2. So it just copies itself to whatever we pass in. So then we'll say 2 dot position equals, actually we'll say dot set this dot position. And what that will do is it'll just copy the x and y to this, to whatever is in here, right? So set basically takes in this and then it puts these values into this value. So it just makes them the same. Then we'll say 2 dot scale dot set this dot scale. There you go. And these two utility functions will be very nice to have. Let's go back into our sprite render now. And we have this variable last transform. Inside of our start method, we want to get a hold of that last transform. Remember, we can't do it in here because if we tried to say this dot last transform equals GameObject.transform, we would actually copy it. But if we do this, GameObjects could be null right now because there's no way we can have a reference to GameObject inside of our constructor. The whole reason we have the start method is that we can access the GameObject. So we'll say this dot last transform equals GameObject.transform.copy, which will copy the transform into our transform. Now we have a copy of the transform, and inside of our update method, we want to check and see if that ever changes. So let's actually go into transform. We will do one more method real quick. This is a method every class has, which is public boolean equals, and it takes in an object O. This method is exactly as it sounds. It just checks and sees if this is equal to O. So what we'll do is we'll say if O equals null, return false. Definitely doesn't equal it. If O not O instance of transform, return false. If it's not a transform, then there's no way it could be equal to this either. Then if both of those are true, we'll say transform T equals transform O. We know it's safe to cast now because we've checked that it is a transform. And then we'll just say return T dot position dot equals this dot position and T dot scale dot equals this dot scale. So now we can check and see if two transforms are equal. This will check and see if they have the same position and scale, which means it is the same. So inside of here, we can say if not this dot last transform dot equals this dot game object dot transform. So if the game object's transform has changed in any way, its position, its scale, whatever, then we will know because this contains the last transform that it was. So if that did happen, what we're going to do is we're going to say this dot last transform. Actually, we're going to say this dot game object dot transform dot copy, and we're going to copy it to the last transform. So we'll copy that data, and then we will set our flag is dirty equals true because something has changed. So let's go up here now. We'll say private boolean is dirty equals false initially. So we know that we are dirty now because something has changed. Also, let's go into here. This dot is dirty equals true if they set the sprite to something new, and if they set the color, of course, it's also going to be dirty. And let's actually be a little bit more wary. We don't want to set to dirty if they just do this. We'll say if this dot color dot equals color. So if they are not equal to each other, then we'll set it to true. And in fact, let's not even copy it. So if they're just trying to change the color and it's the same color that it already is, there's no point in even setting the color because it's just the same thing. And then we'll worry about sprite another time because this contains a little bit more data than I'm willing to work with. And this is fine for now. We'll just set it to dirty every time the sprite is changed. But yeah, that should now set a sprite to dirty if any of the data that we care about has been changed, minus the sprite, of course. Well, I mean, it will set it to dirty. We just aren't checking to see if it's the same sprite that they're trying to set it to. But that's good enough. Let's go into render batch now and actually implement our check so that we check and see if any of the sprites are dirty and we fix it if they are. So up here, we'll go to our render method. Before we actually bind the buffer, and actually we're buffering all the data anyways every frame, which is good, but nothing is changing in here, right? So before we do that, what we're going to do is we're going to say for int I equals 0 till I is less than sprites dot size length I plus plus. So we're going to loop through all the sprites. Then we're going to say sprite render SPR equals sprites I. Then what we will say is if SPR dot is dirty, and we will get a function real quick for that. So we'll go into here and we'll just say public boolean is dirty, return this dot is dirty. Then let's also do public void set clean, this dot is dirty equals false. So we'll have a clean method too. So back into the render batch. If the sprite is dirty, first of all, what we're going to do is we're going to say load vertex properties I, then we can say sprite.setClean. And then let's also have a flag up here. We'll say boolean rebuffer data equals false. Then if any of the sprites are dirty, we'll say rebuffer data equals true. Then down here we'll say only if we have to rebuffer the data should we do this. And then we will copy that. I'll get rid of that since we are not doing it every frame now. So that's pretty simple, right? We already have this function load vertex properties that does everything we need it to do, right? This is the reason also that I abstracted this into a function, because this is really nice now when we need to rebuffer data. So this basically just finds the sprite that we're using right now, and then it loads all the appropriate vertex data because we did all that stuff already. So now we can reuse that functionality in here and say if it's dirty, then we need to reload that data once again. Then we just say, okay, now that sprite's clean, let's rebuffer the data now. That way, the next frame comes around, if it hasn't changed, we won't rebuffer it again. Then we just check and see if we have to rebuffer any data. And if we do, we buffer the subdata, which is really just the whole vertex array for now, which is also fine. Let's check and see if this is actually working now. Let's go into our test scene or our level editor scene. And inside of update, I have this camera movement thing, which I don't know if I ever went over that, but get rid of that. And let's make object1 a variable that is global to the class. So we'll go up here and then we'll just say private game object obj1. Then inside of our update method, what we'll do is we'll say obj1.transform.position.x plus equals 10 times dt. And let's see if he starts moving. So we'll go back up and we get an error. So what's happening here? This was a dumb mistake of me. So I said if for int I equals 0 till I is less than sprites.length, that's not actually how many sprites we have. We only have number sprites of sprites. So we should actually loop until we reach the amount of sprites that we actually have in there. So let's do this one more time. And look at that, Mario is moving. This is really cool, guys. This means that we can now do a lot of stuff that allows us to build a game, basically. And you'll notice that he's actually like slowly disappearing. That's because, let me actually show you this too, because I don't want you guys to think you have bugs in your code or something. This is totally okay. If we go to the window and we change the clear color from black, we'll change it to like a soft red. So I'll just do like that and then something like that. So if we change the clear color, we'll notice something. Look how the black behind Mario, this is actually all the alpha values, right? This is where it should just be disappearing, right? Because we have a texture that has some alpha, but our game engine currently can't handle alpha values. The reason being is because of something called blending, which we will get into actually probably in the next tutorial, because that's a good segue. So yeah, we'll do that in the next tutorial, but that is not a bug in your code. Let's go back in a level editor scene and do one more thing that I think would be cool. Let's do a little animation real quick, because we do have the ability to do that. So I'm just going to go up here, say private int sprite index equals 0, private int sprite flip time equals 0.2f. That's a float, and I said that was an int. And then we'll say private float sprite flip time left equals 0.0f. Then inside the update method, this is basically just going to be a little animation of Mario. We're going to say if sprite flip time left is less than 0, we'll actually do less than or equal to. Then we're going to say sprite flip time equals sprite flip time left, and then we're going to say sprite index plus plus. Then if sprite index is greater than 4, sprite index equals 0. And we are also going to in here say obj1 dot set dot get component sprite render dot class dot set sprite, and we will say sprites dot get sprite, I think we called it I. And then let's go into, or actually sprite index. Let's go up here and make this sprite sheet a global variable to our class too. So we'll say that sprites, and this is all just test code too, so don't worry about how it works necessarily. I mean, we're just moving the sprite across every 0.2 seconds. Oh, and this is backwards. This should be sprite flip time left equals sprite flip time. There we go. Then this should basically flip Mario so that he's doing a little animation. Let's see what happens. So he's in this pose and then he's not changing, which is not right. Oh, and then we have to do one last thing. We'll say sprite flip time left minus equals dt, so that we actually move it according to how much time has passed each frame. There we go. And look at that. We have a little animation. Mario is running, and he's not really. We're switching the sprites, which is how you would do an animation. So that's a cool little thing that we got done in this video. Now that we know how to rebuffer all the data and everything, that's about it for this tutorial. In the next tutorial, like I said, what we will be going over is alpha blending. Like I said, this series, we are doing a lot more stuff manually than we have in the past. And that includes how we actually blend the alpha, which I will explain in much more detail in the next tutorial. In the last episode, what we covered was a dirty flag system, which basically means that we only update data that is necessary whenever things change in our scene, and then we send it to get redrawn. In this tutorial, what we're going to be covering is alpha blending. Alpha blending is something that we have to do manually. Basically, what it means is when you see the alpha channel of an image, you typically think of that as transparency. But the alpha channel can actually be used for a variety of things, and you can actually do transparency in a variety of ways. So we're going to take a look at the most common way to do transparency so that we get the result that you would expect, and then we're going to talk about future improvements that will need to be done to ensure that it always works correctly. So let's take a look at how alpha blending works, and then we will code it. So before we begin to code this, I do want to take a look at a concrete example like always. Now, what I have here is a couple images that I have also imported into my assets folder for this game. It's just a green and a red square with some half alpha. Now, if I asked you which was on top of which, you would probably be able to guess that this red square is on top of this green one, and this green one is on top of this red one. But why do we know that? Well, that's because of the way that these are blended. They're blended using a specific function. Before we begin to talk about this, let's get some terminology down. Whenever I talk about the source, I'm talking about the original image. So this would be like R source, G source. Whenever we're talking about the destination, RD, GD, we are talking about this final color. And so the way that alpha is typically blended is we use this function that's 1 minus the source alpha, or I guess that would be AS with the way I wrote it. And basically all that means is that our final color, so we'll say color final, is equal to our destination color, so whatever color is currently in the destination, times the source alpha plus the new color, so color source, times 1 minus the color's source alpha. And so what this ends up happening is, so in this case, let's actually just work out a concrete example real quick. So this color right here would be equal to, so color final would be equal to, color destination is green right now, so that would be RGB, so it would look like that, times source alpha, which we'll say is 0.5, plus the source, which is red, which would be RGB times 1 minus the source, which would also be 0.5. We'll do 0.6 just to make it a little bit more interesting. So this would be 0.6 and this would be 0.4. Then when we multiply that out, what we end up getting is color final is equal to 0.60 plus, and this would be 0.400, which equals 0.60. And let's take a look at what that looks like real quick. And if we take a look at what that looks like, it would end up looking something like this, which I'm trying to bring over so that we can sort of compare, which actually looks a little bit more like this one, which means that maybe I have my source and destination mixed up. But regardless, you use this thing called a blending function, which looks something like this. And then that blending function is used by OpenGL whenever there is alpha channels included. So the one final complication that we have to worry about is, as you can see, this green one is behind this red one, and this red one is behind this green one. And how do we control what's behind what? Well, we have to use something called the painter's algorithm, which basically means you draw everything that is furthest back first, then you draw the next things, then you draw the next thing, sort of like layers in Photoshop. And this is really simple to do. We've done it before, right? We just use something called a z-index. And using this z-index, we can determine which layer our sprites are on. We'll have integer values, so we'll have them ranging from -2 to 2, which gives us a total of 5 layers, which should be sufficient. Then we can basically draw the layer on -2 first, then -1, then 0, and so on and so forth. If we have 2 on the same layer, we just draw them at the same time. And the way we'll be doing this is we will just be giving our batches a z-index, and then that z-index will only contain sprites that are using this z-index, and then we will sort our batches according to z-index, and then we will draw them in that order. So we will take a look at how both of these things work in this tutorial, and let's actually just start coding so that we can get this done. All right, so remember we got to this point last time where we just have these Marios running, and just to accentuate the point that alpha is not being blended right now, I'm going to do this real quick so that we can see it's not working. Now, to enable blending in OpenGL is actually pretty simple. We just go into our window class, which I'm already in. Then we go down, and after we have created GL's capabilities, we will say GL enable blend. Then, and it's going to say, actually, this is GL blend. And then we're going to say GL blend function. So we're going to set the blend function. The S factor is 1. So remember we said it's the color destination times 1 times source alpha. We just use the source alpha. Then the D factor will be GL1 minus source alpha, which is the most typical thing that you can have. You really shouldn't have to use anything other than this unless you're doing some fancy stuff. Now, literally just doing this, if we run it again, look at that. We have our alpha blended, but there is that one other problem that I talked about. So let's take a look at how that works. I mentioned that I had those 2 squares inside of my assets folder now, so I will use those, and if you want those, there's a download link in the description. Now I'll go to the level editor scene, and instead of using this sprite render, I am going to say we're going to use a new sprite and a new texture, actually asset pool.get texture. And I'm going to go asset/images/blend image1.png. And that's not a semicolon. Then I'm going to go ahead and copy this and paste it into this one as well. So right here. And this is blend image 2. Then I'm going to go down here, remove all this stuff we were doing with the animation, because we no longer need that. And yeah, that should be good. So let's run this one more time. And you'll see we get nothing. That brings me to another point that I forgot to mention. Well, I didn't realize it happened. We do have a bug. So if we go into sprite render, our dirty flag system should set our sprites to isDirty is true when they are initially created. Otherwise, as you just saw, we will never see anything, which that's not good. And then that fixes it. So if you had problems with sprites disappearing, that's why. Now, we can go back into our level editor scene, and you saw we had the 2 squares. Let's move the one on the left so that it is over the one on the right. I'm just going to move it to 200. And what we'll see is the green is on top. So you might say, hey, that looks fine. What's wrong with this? Well, this actually has to do with the order they're currently being added. Because right now, we were drawing the red one first, then the green one, which meant that the green was on top. But if we draw the green one first, then the red one's now on top. This is a problem. We want to be able to have reproducible results every time, no matter the order we add the game objects, where one object is in front of the other, guaranteed. And so that is where z-indexing comes in. So to implement z-indexing, it's actually not too bad either. Let's just go into our game object first. And we're going to create another private variable. We will call this private int z-index. So every game object will now have a z-index as well. Go into here and we'll say that they are required to pass in a z-index also. And we'll just say this dot z-index equals the z-index. And up here, if they don't pass in anything, we'll just say this dot z-index equals 0. And then we'll go all the way down to the bottom and create a getter function. So we'll just say public int z-index, return this dot z-index. now we can use that. So let's go into our render batch. Our render batches are also going to have a z-index so that we can tell what z-index they're on. So we will just add a z-index to them, and then when we create a render batch, we'll say you need to pass in a z-index, and then we'll just set it equal here, and once again create a getter so that we can use that. So we'll just say public int z-index, return this.z-index, which is nice. And then we'll go into our render. This is where all the heavy duty is going to go in, the heavy duty stuff. So what we're going to do is right here, you see that we need a z-index now. And so if we're going to create a new batch, what we're going to say is it's actually going to use whatever sprite we're adding. So sprite.gameObject.z-index is the z-index we will use when we're creating a new batch. And the reason we'll know that's true is because first we're going to check if it has room, and we're going to check if the batch.z-index equals the sprite's gameObject's z-index. This way, we only add sprites of the same z-index onto the same batch, which is good, because now we will have a z-indexed system. But that doesn't solve all our problems, right? So now if we go back into our level editor scene, and I'm going to say I want I think this is the green, I want it to be on the bottom. So let's go, I'm just going to enter that down so that we can see. Give him a -1 z-index, okay, right? So he should be on bottom. And then I'm going to give him a 2, so he should definitely be on top. And the green is still on bottom. I believe this is the green one. I'm getting confused now. Okay, yeah, so blend image 2 is green, blend image 1 is red. Note to self, name better names. So I have the green on bottom, which I also have in the z-index, but let's change this now. So we want it to be on top instead, right? So we put 4. Well, the green's still on bottom. Why is it not working? They are getting added to different batches. I can guarantee you that, but we're not sorting the batches. So if we go back into our renderer, we add all the batches and stuff, and then we just render them in the order that they were created. So what we need to do is create a way to sort the batches, and we'll use Java's standard library for this because it's just simpler than writing our own sorting function and everything, which I would suggest we could do in the future because it's fun. So what we're going to say is this class implements, I believe, comparable, and we're going to say render batch. So then it's going to give us an error. Nope, we'll say this extends, maybe. Oh, I'm doing this on a function. Up here at the class, we'll say this implements comparable render batch. Okay, and then it's going to say we must implement this compare to method. So I'll say okay, and it will create this. Then what we'll do is say we'll return integer.compare this.z-index to o.z-index. And all this is going to do is it's going to give us a way so that we can compare two render batches based on z-index. So if this z-index is less than this one, this function will return -1. If this z-index is greater than whatever render batch we're comparing it to, it will return +1. If they are the same, it will return 0. And that's sort of Java's basic sorting system way that they compare objects. Now let's go back into our render, since we have this ability to compare objects, and we can use Java's collections sort method. So, and we can say every time a new batch is added, we will just sort the batches. So we'll say collections.sort, and then we'll say batches. And what this will do is this will sort our batches every time a new one is added. That way they are always sorted in the correct order. So now if we do this, green is on top. And once again, just so we can reiterate what just happened here, we will now change this. So this is 4, this is 2. We'll change this to 1, should now be behind. It is now behind. We will change it to 2, and now it's going to be behind, but that's just because of the order. So now they're on the same layer, and now if I move this, so now if I add it after I add the first one, we will see that it's going to be on top because it's on the same layer. This has nothing to do with the z-index. This is just because they're on the same layer. And then if we want to control specifically what order they are, then we can go and change their z-index. And once again, all we're doing is we are just giving our batches a z-index, and then we are only adding sprites of the same z-index as the batch to that batch, and then we sort the batches, then we draw the batches in sorted order. That's all that's happening. So it's just some basic computer science algorithms to give us the result we were looking for. And another thing that we can do that's kind of cool is we can also do collections.reverse order. So now we will have our batches sorted in reverse order. So if we go into our level editor scene, this should be behind. So green should be behind red, but green is in front of red because we're sorting it in reverse order. And then if we do this, then it'll go behind it. So that just reiterates this point that we are controlling this. We are controlling everything that's happening here. And so I would like this to remain in sorted order so that we can control that specifically. But yeah, all this to say, we now have alpha blending and we now have z-indexing, which are two pretty big components. Now, there is a problem. Like if we try and change a sprite and we change its z-index, there will be problems because we would technically have to remove it completely from the batch that it's in because it no longer belongs in that batch. And then we have to add it to a whole new batch. We'll look into methods of how to do that stuff in the future, but for now, I think that's good. Now that we have a basic rendering system done, though, I think it's a good idea to start building our GUIs. So what we're going to do is in the next tutorial, we're going to start getting ImGui up and running, and then we will begin looking into how to use that to build some GUIs that we can create a level editor with. In the last episode, what we did was we covered z-indexing and alpha blending, which is a very important feature for a 2D game. In this episode, what we're going to be doing is integrating ImGui into our game engine. So right now, you should be seeing something that visually describes what I'm talking about. Basically, ImGui is this whole different graphical user interface, which basically means immediate mode GUI. And it's different from the typical approach, which is a retained mode GUI. And the main difference is, as you can hear in the names, the difference between retained mode and immediate mode, which basically means that instead of building up a whole complicated structure for your GUI and everything, what you can say is declare items in real time that you're going to have onto your GUI, and then have immediate changes affect your real-time application, which is perfect for a game engine where you have real-time needs like this. So it's just the preferred approach for indie game developers, and even Unity uses the immediate mode GUI paradigm because it just works and it's really nice, and you don't have to mess with callbacks and everything, which is really a pain when you need immediate feedback for your GUIs for your games. So I'm going to take a look at a couple different ports for the Java version of ImGui. And I'm going to explain why I'm choosing the one that I choose, and then I'm going to also explain how you can use it with a jar if you want to use a jar. I will mention the other version that does have those easily accessible for those of you who want to use jars or Maven. But I will also tell you why I think that it's probably a better idea to stay away from the other version. All right, let's get on with checking out the different versions, and then we will actually integrate this into our game engine. Before we actually begin integrating ImGui into our system, I do want to talk very briefly just about the difference in the paradigms. So the standard approach to graphical user interfaces, GUIs, is using something called retained mode. And retained mode basically means you have a tree site type structure that you build up of all your elements that consist of your visuals. And so the most stereotypical tree structure that you can think of is the DOM, the document object model, that is part of websites for HTML and CSS and stuff like that. So they build up this big structure. You have the HTML tag, which has a head tag, a body tag. The body tag can have several div tags. The div tags can have any of the other tags and everything. And you build up this complex structure, which basically says this is how I want to lay out everything, and this is how everything will be laid out, which I'm going to add is super helpful for styling. Like if you want to make a really complex style and make it look nice, this lends itself very well to that because you know exactly where everything should be in relation to other things. But the drawback that comes with this is you no longer have immediate functionality to any one of these divs. You have to go through a very big layer of indirection to see if something happened all the way down this tree. And so to get around that, they come up with these things called callbacks. So if you have a button on your page and you want to check and see if this button was pressed, you have to set up a callback, which in JavaScript is actually pretty nice. It's easy, it's simple, but even in JavaScript, I think it just provides this layer of indirection where you know as soon as this button gets pressed, you want something to happen immediately, but you have to go through this layer of indirection through a callback, which means that when you're trying to trace your code and stuff, all of a sudden you start getting lost as to what's happening because you're like, okay, why is this function getting called? Where is it getting called from? And everything like that. So that's the typical approach to GUIs. Now, ImGui, this is a gross oversimplification, but basically you can think of it as having a list of elements and it rebuilds this list every frame. That's not true too. Smart ImGui systems and everything cache stuff and everything and have ways to get around that. And then to build some sort of structure with ImGui, you would basically say begin, and that would start a window. And then you would say stuff like if button, and this is what the button says. And then you could handle what happens if this button's pressed inside here. And then you could do a bunch of other stuff. You could do scroll bars, edit, whatever, color edits, text edit, everything. And then you just have this end, which says I want to end this function. And so the reason it's called immediate mode is because this is very similar to OpenGL's immediate mode graphics API, but this is not the same thing. It is not like OpenGL's immediate mode graphics API. All this means is that we have immediate access to be able to draw these, but like I said before, if you have a smart ImGui system, it will be caching elements and stuff. But yeah, so that's the basic difference. And as you can see, this is much more succinct, especially in a real-time application where you know exactly what you want to happen when somebody clicks on this button because you just created this window. And like I said before, lots of people discount this thinking that it can't be used in complex systems. Unity. I don't really like the game engine that much for other reasons, but Unity uses ImGui and it's a pretty complex graphical user interface, right? Like there's thousands of tools written with Unity. I'll link an article in the description that sort of explains the difference between these two as well, and he's talking in terms of React and Redux. But that's about it for the difference in these paradigms. Now let's actually take a look at some things that we can use to get ImGui running in our game engine. Alright, so the version of ImGui that we're going to be using is originally written in C++, so we are going to be using some bindings to it. Now I'm going to recommend this repository on GitHub just because I tried to use a different one, which I recommend in some of the comments of my last video on ImGui. This one specifically, Kotlin Graphics. And it's not bad. It's not bad, but there were some problems with it that I found irreconcilable. So, first of all, in order to use this one specifically, you do have to include the Kotlin runtime library. So, it's kind of unnecessary because our whole game engine's in Java. You know, you don't want to have to include a whole nother runtime just because of one library that you're using. So that's my first kind of hit against it. And then my second hit is no matter what I could do, I could not get the fonts working right. And having a different font, especially on my screen, the higher resolution you have, the more important it is that you can rescale fonts and stuff. And for some reason, their true type binding was not working correctly. So I have no idea what's wrong with it, but it just was a pain to start getting together and everything, and that stuff wasn't working right. So if you want to, go for it. You can use this, totally. Just remember you have to bind the Kotlin runtime library with it, otherwise it will not work. Now with this one, the problem that a lot of you had was, first of all, it does not have a Maven port, which does kind of stink. And then another thing is some of you wanted to use jars instead of using Gradle, and that's fine. If you do want to use a jar with this, I would suggest cloning this whole entire repository and then building it yourself, because some problems you might face with that is different build versions and stuff. He doesn't have any jars too, by the way. So that means you would have to build it yourself anyways, but that's probably better because then you can have control over which version of Java you're compiling with and everything like that, which is good. Now, if you're just don't want to use Gradle because you don't want to use a heavy-duty editor like IntelliJ or something, let me know in the comments because I can go over a quick tutorial on how to use this without using IntelliJ. It's actually not that bad, and Gradle is actually super helpful. The way I like to think of it is it's sort of like NPM, Node Package Manager, for Java, except a lot smarter, I think, because you can actually do strict versioning and everything like that, which I guess you could do with NPM too, but that's besides the point. So this is basically just like a package manager where you can install packages and stuff, just one easy to use thing. So let me know in the comments if that's the reason that you guys are shying away from this, and if it is, then we can go over that in a separate tutorial. But we will be using this, and the first thing that we are going to do is we are going to copy some of this stuff into our build.gradle file to get this running. So I have our project open right here, and I'm going to go into the build.gradle file because we will be making a few changes to this. Let's go back up to here. You'll notice that they have Maven Central and JCenter. I'm not sure we have both of those. So yeah, we've got Maven Central, but we don't have JCenter. So let's add JCenter up here. Just copy and paste that. And then we'll go back up here once again. These are the two ones that we are mainly concerned with. So implementation, this is all LWJGL stuff, which we already have. Actually, yeah, let's include this one too. This is runtime dependencies, but then this is all LWJGL stuff, which we already have. So we'll copy all that, go back into here, and we will just paste it all right here. And we'll say ImGui stuff. And then we'll go down here just so that we can separate this. This is LWJGL stuff. And we don't really care about the Linux natives or the x86 natives unless you're running on those. And if you are, then please keep those because those are important. Let's go back to here, and he says we should use this version. So we'll copy this, and then up here we'll say project.x.imgui version will be 1.76-0.9, which should resolve this unknown variable right here. And then we should have our runtime natives, and then we should also have our bindings right here for the ImGui library. So then you'll notice his Gradle projects need to be imported, hit import changes, and we should be able to see, well, if you have your build up down here, you would be able to see it, but that just imported successfully. So if we run this, we should still be able to run it with no problems in our Gradle file. Now let's actually look at how we can get this up and running in our project. First thing I'm going to do is I'm going to go into here and just create a new class, and I'm just going to call this ImGui layer, just to sort of separate all this code, because the one other downfall of this specific repository is you have to do a lot to get it up and running, but it's really not that bad because he gives it all to you. So it's just a bunch of copying and pasting. We'll click onto that ImGui GLFW example. Do that one more time. So click onto this because this is where he shows us his entire example file, and you'll notice that this is just a giant example of how to use it. So what we're going to do is we're going to copy this whole function, and then we're going to start removing stuff too, so don't worry. We're going to copy all of this because this is the init ImGui function, and we're going to go back into here, and I'm just going to copy and paste that all into here, and we will say this is a public function. Okay, and then if we take a look at these errors, these are just import errors. So if I hit Alt-Enter, say import static, and then it'll eventually just import all of them. So that's good. This is a local variable that we will need to get. Window pointer is something we will need. That is just our long number, which is our window ID, basically. And then if we look down here, this load from resources we don't have. I'm just going to comment all of this font stuff out for now. We will be using this in a little bit because I will show you how to change the fonts so that you can use actual nice fonts if you need something else. And then this is a local variable as well, and GLSL version. You can find that just by going into one of your shaders to see which version you are using. So if we go into here, we are using GLSL #version 330 core. So we'll just paste that into there instead. Now let's actually get these local variables, the window pointer and the mouse cursors. First of all, window pointer, that one's kind of easy. When we create an ImGui layer, we will take in a long, and we'll call this GLFW window. And then we will store a private long, and we'll call this GLFW window. And then we will just set it equal in here. So we'll say this.glfw window equals glfw window, copy that, and we're going to paste that everywhere we see window pointer. So instead of that, we're going to say window pointer, we are going to say glfw. And what this is this is basically setting up the callbacks for ImGui, which means that we may also have to do some extra work to get our callbacks to work properly because ImGui might consume them. So we'll take a look at all this stuff in the future. Next thing we need is the mouse cursors, which if we go back up into his example, he has a bunch of different things, and we'll notice mouse cursors is one of them. And this is the impl, so we'll get this, the ImGui impl GL3. So we will get both of these, copy them, and then we will go down here and paste it, which is good. And we have no more errors, so that's good. That's the first part. Now, the next part, that was just for initialization. We do want to get destroy, and we want to get the loop, which is how we actually render stuff and everything. So let's scroll down to the loop, and you'll notice that he has this ImGui new frame, example UI render, and then ImGui render. Let's copy the start frame, which is this thing right here, and the end frame, which is this thing here, and we'll just copy all this. So start frame and end frame. And then for destroy ImGui, we will, let's just copy all this stuff. So we will copy all that. And we will paste it into here. We're going to get some more errors. We know this is just GLFW window. So we'll copy that, paste that. And let's actually remove the swap buffers and pull events because we don't want to do that inside of our ImGui layer. We just want to render it. So just take those out. And let's replace all these window pointers right here. Let's take out the clear color because we also don't want to clear the color in here. We just want to do our ImGui stuff. And inside of here, instead of the win width and win height, we're going to say window.getWidth and window.getHeight, which we will implement in just a moment. Then here we will also say window.getWidth and window.getHeight. And then for the mouse pose, we will say these are actually just float mouse pose x equals 0, and then we'll say float. Actually, this is an array, mouse pose y equals 0 like that. And we'll fix this one too real quick. And the way I know all this stuff too, I'm not just pulling this out of nowhere. Basically, if you look down here, you'll notice he's using it down here too. So I just noticed that was an array. And so that's probably what we want to use. And then if we look at this function, it says it takes in a long and then a float and a oh, it does not take that. Okay, so it takes in a long and a double and a double. So these should actually be doubles, which is simple. We'll just fix that. There we go. And then we get no problems here. And then the way I knew he was talking about win width, this is just the window width. FB width is the frame buffer width, and we're just going to set that to window.getWidth as well. And let's actually make this even easier too. We'll just say float win width, which he's using as an array. So we'll say win width equals window.getWidth. And then we'll say float win height equals window.getHeight. Yeah, and then we can actually remove these get window size and get frame buffer size. We don't actually really even need those because we will be getting the width and the height from the window directly. So let's implement those functions real quick. They should be fairly easy too. We'll just say public static float get width. And actually, I'm going to change this to an int. So we'll say this will just return get.width. And then we'll say public static int get height return get.height. So we're basically just returning the window width and height in there. Nothing too complicated with these. And then with this, I'm just going to replace this with 1, 1 because this is the scale he's setting, and he's basically setting it according to the frame buffer to the window scale, which we don't really care about because it's going to be the same in our case. Okay. So that was a lot of just sort of random stuff, but according to his example, it's all needed to make this stuff work. But don't worry, we're almost done. Last thing we're going to do is we're going to create a public void update, and this is going to take in a float dt. And what we are going to do inside of here is basically what he is doing inside of his loop. He says start frame, delta time, ImGui new frame. We'll just copy all this stuff. So copy that, paste it into there. We're using dt, not delta time. We no longer need to cast that. And we do not have an example UI. So we will talk about how we could switch this stuff up and everything too in the future. For now, let's say imgui.show demo window, which will show their demo window. So we now have this update, we have the start frame, we have this end frame, which is also being called inside of here, and this new frame and this render, which is just all required by ImGui. Okay, let's actually try and set this up and see if it's going to work right. So we'll go into our window. Then at the very top, what we're going to do is we're going to say private ImGui layer, and then inside of here, after we create GL's capabilities, we'll say this.imgui layer equals a new ImGui layer, and we will give it the window pointer. And then we will say this.imgui layer.init. That way we initialize it. Then inside of our loop function, right before we swap buffers, we'll just say this.imgui layer.update. And we will pass it delta time. Okay, let's run this and see what happens. There we go. So we get this demo window, which means that we have integrated it successfully. And you see that my mouse is not actually getting picked up by it, which means that we have done something wrong in terms of the mouse callback, because it's not actually getting my mouse. So let's take a look at what's going wrong with that. Okay, so it turns out our mouse is actually working fine. So the only problem is, you'll notice it only works when we're in minimize mode. And the reason for that is because we just have the mouse position being set wrong. So what we need to do is set up a window resize callback. Basically what's happening is right here where we say get the mouse position, it's getting it as if we had the window width and the window height, but we're never changing the window width and window height when it maximizes. So we need to fix that real quick, which means we just need to send up a new event callback here. And what we'll do is we'll just inline it. So we'll say set window size callback, and then we're going to give it the window. Then we're going to give it a lambda expression. And I'm going to take that. And this lambda expression is going to take in a window, a x offset, and a y offset, which should be good. Then we'll literally just say this dot get. We'll say window dot set width, because this is actually the new width and the new height, not x offset and y set offset. Okay, so then we'll say window dot set width new width, and we're going to say window dot set height new height. And then we will create these functions too real quick. We'll just go down to the bottom again, say public static void set width int new width. We'll say this dot get, well, not this dot get, we'll just say get dot width equals new width. And then we'll say public static void set height int new height, and we'll do the exact same thing. There we go. And now every time the window is resized, as in it's maximized or something, it will go through this callback. We will actually have the appropriate width and height inside of these variables, and you'll notice that our mouse is actually working now. Another thing you're going to notice is the text is super small. That is a little bit heavier. If you want to take a look at it yourself, it's going to be inside of this ImGui layer right here where we comment all this stuff out. Try and get this working as an exercise, but unfortunately we are kind of running out of time for today. This was sort of just getting ImGui integrated. We weren't really trying to learn any new concepts in here, but in the next tutorial what we're going to do is we're going to actually start setting up something more than just this demo window. So like you saw in the example, we're going to actually set it up so that we can start using ImGui in our scene and on the active game object, all that stuff. So in the last episode, what we did was we integrated ImGui into our engine. So now we have the ability to use ImGui, except we're still missing a few key features. So in today's episode, the first thing that I'm going to do show you how to import your own font, because that is super important. And we want a good font so that you can either change it up just to your liking, or you can resize it so that it's a little bit bigger if it's too small on your screen because of DPI issues and all that stuff. And the next thing that we're gonna do is actually fully integrate ImGui so that we get a good scene integration so that we can override methods like we do with our update method and have each of the game objects call ImGui when it is selected or active. So we'll take a look at how to do all of that in this episode. All right, guys, so we're actually going to jump straight into coding. I don't feel like there's much of a need for drawing anything out because most of this stuff is fairly straightforward. Now, the first thing that we are going to do, let's restart this just so that we can see where we were at, because this will let us see what the first big problem is. So first big problem, for me at least, for you it may not be, is the font is way too small. But it may also be a font that you just don't want. So let's take a look at how we can actually change up that font fairly easily and get it working. So I'm going to go into ImGui layer, uncomment all this font stuff, and then we will go through and just sort of pick and choose what we actually need. So the first line, the IM font atlas. What is the font atlas? Well, this is basically just an atlas, or a sprite sheet is probably what you know it as better, which contains all alphanumeric characters and punctuation marks like this. And this is what ImGui uses to do the font rendering. So it creates a big sprite sheet of all the characters, and then it just selects those and places them onto quads to render the font, which is actually what we will be doing in the future too, for like HUD items and stuff, but we can just use this for now. So it creates a font atlas, then we need to get a font config, and let's take a look at this comment. It says it's natively allocated, so it should be explicitly destroyed. And we'll notice at the bottom here, he has font config.destroy, so we'll keep that. It's good to have that comment just so we know too. Then we have this font config.set glyph ranges. Now the glyph ranges is basically what type of characters you want. So you can see that he's adding in the Cyrillic character set. I'm gonna say we'll just stick to the default range, which is US ASCII. I'm fairly certain, I'm not completely certain on that, because I don't need Cyrillic characters. If you did, you could change this so that you have the Cyrillic characters, or I think we'll check. They have Chinese full, Chinese simplified, Japanese, Korean, Thai, Vietnamese, and you could come up with your own custom glyph range, because you can see that this is actually just a short array, which basically means that all it's taking in is just a array that looks like this and contains the range for the glyphs. So we're just going to do the default though. Next line, he has font atlas.add default font. We don't want the default font, or at least I don't. So I'm going to take that out. And if we take that out, we're actually going to see, I'm going to comment out this line, and all of these, because they all add fonts using stuff we don't have. If we don't have a default font, what ImGui is going to do is it's just going to crash, and we'll see up here that it actually says it failed with an exception, assertion failed, atlas config data.size greater than 0. So it's saying, hey, you never gave us any data for the characters, we can't render anything because we have no fonts. So we will now set up our own font. Okay, so you see that it says set merge mode. What this does is this basically means that anytime you add a new font, it will merge it to the font atlas and just add it for characters that we may want. I'm going to take that out because you can't merge fonts if you don't have a default font, or you can't merge fonts if you're only adding one font. If you had multiple fonts, you would set that to true, but I'm going to set it false. I'm going to take this out too, and I'm actually going to take all of these ones out too. They're just different ways that you could load fonts, different examples. We're just going to do the simplest one, which is using the STB TrueType library. So it says add font from memory TTF, which is actually not the one we want. This is a little bit different than what we want. So we'll say font atlas.add font from file TTF. Then we can just pass in the file. I'm going to say assets/fonts/sago UI.ttf, which I have included into my directory. Actually, I might not have included it in there. So if you want to add a custom font and you are on Windows, I would say go to local disk C, Windows, then you can go to fonts find a font you want. I'm going to do Sego UI, which is right here. And then I'm going to click onto it, and let's see, I'm going to click just the regular, wherever that is. There we go, regular, copy it. Then you'll go up to your project directory. So mine is in C, Dev, Java Projects, and Mario. And then I'm going to go into Assets. Okay, I do have fonts, and I do have Sego UI. But if you didn't, you would just paste it here. Now you have it. So now we have this font file. Then we're going to say the size in pixels I'm going to do is 32. And the font config is the font config that we created. That should be all we need. Now, if we run this one more time, we should get the window, and we have a bigger font. And you can see this is true. I'm going to do it to something outrageous like 64, and you'll notice this gets really big. So that is too big for me, though. 32 is just fine. Now, this demo window is sort of how we are going to go about figuring out how to do things. So I will show you an example of if I want to do something, how I figure it out and everything in just a moment. First, let's set up ImGui so that it actually is fully integrated with our scene. So right now we're saying every update, we start a frame, we do a new frame, we show the demo window, and then we render. I just realized that my mouse capture was off too. So sorry about that first half of the video. But now that that's fixed, we need to add in something inside of here that basically says now we need to do ImGui on our whole scene too, so that we can have custom things. So what I'm going to do is I'm going to go to the game object, and we're going to say public void ImGui. Then we're going to say for component, C in components, C.ImGui. Then we're going to go to component. We are going to create a public void ImGui. This way classes can override it if they want. And I'm actually going to change this too, because our update method, we don't want to make components force them to override or to implement this themselves. They should be able to only implement it if they want it to. So this way we can do like an override in a component, and then it'll override this method. But if they don't want to implement it, they don't have to. So, and then we're doing the same thing with ImGui. Now we have a way to ImGui on our game object, but how does that actually get called? Well, let's go into our scene, and we're going to create a couple functions in here. We'll say public void scene ImGui, and then we're going to also create a public void ImGui. This function is going to work sort of the same way as this function in the component, where you can override it for specific scenes if you want. And then this one will just do the active game object. So we're going to go up to here and say protected game object, active game object is null initially. Then we'll say if active game object is not null, then active game object.ImGui. And we'll actually say ImGui.begin inspector, and then ImGui.end. What is active game object? Active game object is basically the game object that you are inspecting. So say you're in your level editor and you click onto a game object in your level and you want to change some property. That game object is now the active game object. And so what we're doing is we're creating a window by saying begin the inspector, then we call ImGui on the game object, then we end the window so that we have that window. And then we'll just call ImGui after we finish this. This ImGui is something that you can use to create custom scene integrated ImGuis and stuff. We'll see how to do all this too in just a minute. So let's go into the window now though, and we will call, so inside of here we say update ImGui layer, and then what we're going to do is we're also going to pass it the current scene, and then we're going to change this guy. We're going to say take in a scene too. And then right here, right before we show the demo window, what we're going to do is we're going to say scene ImGui. That way we end up calling it every frame, and that all works properly too. Okay, let's go into level editor scene, make sure this is working. So I'm going to go down here and say @override public void ImGui. Then I'm just going to say ImGui.begin test window ImGui.text some random text, and then ImGui.end. We run this and we get a test window with some random text, which is really cool. Now, say you want your windows, like say I have them right here, I exit, you want it so that when you reopen, they are in the same configuration they were before. That's actually really easy to implement with ImGui, and it's something I'm going to show you how to do real quick too, because I find that I like that feature. If you go into the ImGui layer and just go to the top, you'll notice it says io.set ini file name. This is just an initialization file, ini init. What we're going to do is we're going to say imgui.ini, and then we're going to run this one more time. And I'm going to change some things up, move this over here, wait a couple seconds so that that saves, exit. Then if we run one more time, you'll notice they have retained their position. What just happened there? Well, when we tell ImGui a file name, it goes ahead and creates a file wherever we tell it to. Name of that file is right there. If we open this up, you can see that it just serializes all that data. And so we get the position of each window, the size, all that stuff, literally just pasted right into here. And then it just saves that data and loads it the next time we open, which is really nice. So if you want to save your window configurations, use this. If you don't use it. Okay, now that we have that working, we have custom scene ImGuis, we have a window. Let's say I want to change the color of this square through ImGui. So we know that the sprite render is in control of the color of the square currently, right? It has this vector 4 of color. So what I'm going to do is I'm going to go into the sprite render, and I'm going to say @override public void ImGui, and I'm actually going to put this up with my other overridden methods, just that they're all sort of grouped together. Then I want to do a color picker. How do I do a color picker? I don't know. Well, what I can do is I can go to my demo window and I'll go to widgets, look for color picker. Then I will look for what I want. And I really like this big color picker. I want this one. Well, let's look at some of the text around it. This says, we can literally just look at this. It says color widget, color picker right there. So then what you do is you go up to here, say Okernut ImGui, or just Dear ImGui, which is this one. Then we can go, I'm going to zoom in a little bit, into the ImGui demo.cpp. This is C++, but it translates pretty similarly to Java. It's a little bit different, but I'll show you how to work with it. Next, I'm going to say color picker because I want to use the color picker. And you see that we can sort of go through this file and look for something that is similar to what we just saw. And this actually looks pretty similar to what we have here. So if we look at this, you'll notice it says color picker with alpha bar, with side preview, all that stuff. And then if we look here, we see color picker, alpha bar, side preview. So this is clearly the code that is running that little snippet. So we can take a look at this code and see how he did it to sort of get an idea of how we should do it. So I'm going to say, okay, we need to do this ImGui text thing. And I'm going to say we also need to do this ImGui color edit for thing. So let's go back into our code. Let's exit out of here first of all. And then inside of our sprite render, what we're going to do is we're going to say imgui.text color picker. And then we'll say imgui.color picker 4. And actually, you can just do the label here. So I'm not even going to do the ImGui text. Then we'll take a look at what parameters this guy is expecting. Well, he expects a float array of colors. So we'll go up here. We'll say float imcolors equals, and then we'll say color.x, color.y, color.z, and color.w. Then we will pass in this imcolor. Then what we can do is we can say if this function, which basically means this color picker was clicked on and changed. So if this function, then we will say this color, this dot color, dot set imcolor 0, imcolor 1, imcolor 2, and imcolor 3. Then we will say this dot is dirty is true, and that should change our color. Now let's run this again, but you'll notice we don't get any window with this color. Why is that? Well, that's because we don't have an active game object right now. Remember, we have to have a game object selected to be able to see these. So what we can do is we can go into our level editor scene, And we'll just sort of cheat a little bit. We'll go up here and say this.activeGameObject equals obj1. That way we just sort of force it to be this object. Now you'll notice we get a color picker window, and if we change this, you can see that this changes too, but it looks like it's not changing correctly, right? This is black, but this is sort of a grayish. Why is that? That's because we're displaying an image. If we go into here, remember we have these blend images that we were using for testing. I actually spent a lot of time wondering why the color wasn't matching up, and it was just because I was doing an image instead. So what we can do is, instead of saying use a texture, we will just say, because we can also use a color. So we'll say use red. And then we will just set the color to red. Then if we run this one more time, you'll notice it's bright red. And if we change it, it is the same exact color as this color picker right here, which is really cool. So now we have a way to just immediately get feedback and stuff. This isn't very helpful because we're not saving the data, but that would be the next logical step, to save the data so that we can actually change stuff, click onto this, change it, and then get it the way we want, then Control S, and we save our scene. Okay, so I hope you see just how powerful a few simple functions can be. We have a way to do a custom window inside of every scene. We also have a way to do a custom property for every single component that we add, which basically means that we can now dynamically create these windows at runtime based on the objects, change data, and click on new objects, change data, and it all just works, which is so awesome. I think we're running out of time again, so I'm going to wrap up the tutorial here. So this has sort of been an introduction to ImGui. We know how to fully integrate it into our 2D game engine. The next steps I think we should take is to start serialization, and we are going to use Gson, not JSON, Gson, it's Google's version, and we'll take a look at how we can use that to easily serialize and deserialize our data. I think you guys will like it. And then we'll have level saves and everything that we can use, and we can start really using ImGui to start editing levels, creating levels. So I'm excited for the future. We are getting some great progress done. So in this episode, we're going to begin to take a look at something called Gson. This is going to be super useful in serialization and deserialization, which is just saving and loading of levels. If you've ever used Unity, we will be implementing something similar to their level editor, where we will be able to declare components, and we will be able to dynamically generate save data for those components as our game engine runs, and this is going to be super useful. So it's really cool, and I'm looking forward to show you guys how to do it. So let's take a look at what Gson is and how we can use this to our advantage. It's always good to know exactly what problem you're trying to solve before you begin coding and trying to solve it. So what is the specific problem we're trying to solve? Well, that is serialization, or just saving and loading game data. This is literally just transforming some game object that looks like this with its components into some JSON format, some binary format, whatever format you want to use that makes it look like this, where it has the name and it has component 1, and that component has some properties X, Y, Z, so on and so forth. And you basically just turn it into some format that you can then read back in, deserialize, and turn it back into this game object that we have over here. Now, if any of you followed my Geometry Dash series, then you know how we did the traditional method, which was basically we have a base class called Serialize, and this base class has a couple functions. It basically has a function that says Serialize, and then each class creates its own static deserialize method, which basically just returns a game object from wherever the file is currently parsing at. We would have the base component class inherit serialize, and all of these classes would then inherit this serialize method, all the components. And then game object would also inherit from serialize. This is a huge pain in the butt, because what this means is now for every single component you create, you have to implement this serialize method which is probably just a few lines of code anyways, but it's so annoying because you have to remember, okay, I have to make this in a nice way to serialize, which, I mean, you should be thinking about that generally, but it just is a pain in the butt because you can't just code. Every time you create a component, you have in the back of your head, how am I going to be able to make this easy to serialize? I would like to remove that. So this is the problem we're trying to solve, okay? Traditionally, we have to create a serialize method, which then calls into a bunch of functions that says like, okay, save int, the name is velx, and we want to give it velocity dot x. So that's, and then we would do that for the rest of the properties and everything that we want to save. Well, we want to eliminate this completely. We don't want to have to deal with this at all. So that brings me to our solution. Serialization using reflection. Reflection is basically a newer type of paradigm that's in some newer programming languages. Programming languages that are not C, basically is what I mean by that. So Java supports this, C# supports this, Python supports this, basically any language except for C and C++ and some older languages than that too. And all reflection does is allow us to say, hey, I have this player controller class. Hey, what are my fields in here? And then you can say, give me all the fields. Then this will give you, like, if this has some sort of speed variable, some float speed, and it will tell us, hey, we have a floating point variable here. Its name is speed, and its value currently is 0.5f. Reflection also allows us to say, at runtime, I would like to set this speed variable to 0.8f or whatever value you want. So instead of actually coding it out and saying either like a set method or coding it out and turning this basically the initial value into something different, you can literally set up some sort of function that finds this speed variable, loads it from some data that we have in a text file, and then sets it implicitly. Okay? This is extremely powerful. Okay? This is so amazing and just opens up a world of opportunity. We are going to be using something called Gson, which implements this super well, makes it super easy for us to do this. We have to do a couple of custom deserializers and serializers just to help Gson in its way, because these guys are all pretty abstract, the component class, and we want to make sure that we always get it right. But Gson is basically a way for us to say, hey, I have some class, some type, some whatever, I want to serialize it. And then you can just say, hey, Gson.toJSON, my object, and that's a horrible J. And then what this will return is a serialized JSON object. So it would be like my name of your game object, and then it would have all its properties and everything in JSON with this one call. Super awesome. Which, I mean, that's basically what we had in the past, but in the past we also had to implement all the serialized methods in here too. We don't have to do that anymore. It's completely gone, completely eliminated. So the system we will come up with will be very, very powerful, very, very helpful. And one of the reasons that I love these languages, because C++ does not support reflection. Okay, let's get into it. Let's explore Gson a little bit, see how it works, and get it imported into our engine. All right, guys, so I am here at Gson's repository. This is developed by Google, too, and it is completely open source, which is just super awesome, because then if you want to implement this in a different language, you can take a look at how they did it. Now, let's take a look at how they say to download it. They have Gradle, they have Maven, they have jars. It's Google. I would hope they would have all that. So since I'm in Gradle, I'm just going to copy this line, and we are going to paste it into our project. So let's go into our settings.gradle file, or not settings.gradle, build.gradle. And then right above the ImGui stuff, I'm going to say Gson and give it that implementation. And then I will import the changes when IntelliJ asks me to import those changes. We should be good. I'm going to pull up that build window real quick just so that we can be sure. And this should build perfectly fine. All right, we're good. So that's all working correctly. let's actually implement a little Gson thing just to see how it works. So we'll play around with it a little bit first, and then we'll implement it for real. So let's go into our level editor scene. Our goal right now is going to be to serialize an entire game object. We'll see if we can get to that by the end of the video, and if not, that's fine. We will be continuing this in a second part anyways. So let's say Gson. The way we can build this Gson object is through this thing called new Gson builder. And this will allow us to set a bunch of different settings. So I'm going to do it like this because this is how they did it and it looks kind of nice. We'll say set pretty printing to true. And then if you have other objects that you want to do too, then you can do that. .create. Don't forget that .create because that is important. Now that we have our Gson object, let's just see how it works. Let's say JSON.toJSON, and I'm going to give it just the number 1. So we will print this out to see what happens. Let's print it. This is one of the examples they give too, just so you can get started. And we get 1. That's pretty cool. Let's print out a string. Let's print out hello world. See what this does. Do we get the quotations or not? And we get quotations, hello world. So that's cool. That's telling us this is sort of creating a Gson object out of this. Now, one of the important things to note with Gson is you cannot have a constructor that takes in variables. So we will have to change quite a few things because right now our constructors take in variables. This is not how Gson works. So what we're going to do is we're going to work on sprite render first. Let's comment this out and modify it so that it does not take a constructor. Instead, we want the default color to be a new vector4 f1111, and we want the default sprite to be a new sprite that we will also make constructorless. Okay, so we're going to make that constructorless also. And the last transform, I am going to set to transient. And is dirty, I'm going to set to transient. So basically, Gson is able to look through private and public member variables. So it will be able to find all of these. And that's good. That's what we want. But if you add in this keyword transient, it basically is a flag that tells Gson, hey, these are variables we do not want to serialize. And it will ignore these. It will look for these ones. It will ignore these ones. Okay? Let's go into Sprite now. Let's fix this up and do it so that it does not take in any functions. So for the default text chords, we will set it to this guy right here because that was sort of our default implementation. So we'll do this, and then I'm just going to reformat this real quick. All right, so we have some default texture coordinates, and our default texture will just be null. So we'll assume there is no texture, which means they're doing a color or something, which is fine. Okay, go back into sprite render. Now we lose that error, and we're going to have more errors, though, inside of where we use this. So let's go and try and solve these one by one. Sprite sheet. So how do we now do this? Well, we can say sprite is that, and then instead we'll say sprite.set texture, this.texture, and then we'll say sprite.set text chords, text chords. So let's go and remove this, and then we will create these functions. And if you do not want to write getters and setters manually, you can install Lombok, which was mentioned by Mr. Maniac. So Lombok is just a library in Java that basically allows you to declare something like this at getter, and then it basically creates getters and setters automatically, which is nice. I'm fine with typing this out a little bit. It's perfectly cool. We'll go into our sprite and create those real quick. So we will say public void set texture text. This.texture equals text, and then we will say public void set text chords, and we'll take in an array of vector 2f, and this will be text chords. This.text chords equals text chords. All right, so we've got those setters real quick, and this was inside sprite sheet. Now we have no errors there, and we have no errors with texture. So let's run this again. We're going to get more errors. Okay, new sprite render. We cannot do this anymore. Let's do this instead. We'll say sprite render obj1 sprite equals new sprite render. And then we will just pass this guy the obj1 sprite. And then inside of here, we'll say obj1 sprite.set color. And we'll give it one or new vector for f1. If I can type 1001. Okay. You may be like, oh, this is going to make things so much worse too and everything. But don't worry, we won't be doing this feature because we will literally be editing everything from within our level editor. You'll see. It's really cool. Okay. Now we need to do the same thing for obj2. So let's go up here. We'll say sprite render obj2 sprite equals a new sprite render. And then we want to set the texture to that guy. So let's say obj2 sprite dot set sprite, and we want to give it some sprite. So we'll say obj2 sprite, and I'm actually going to change this to render, just that we're clear about the difference. Then we'll say sprite obj2 sprite equals a new sprite, and then we'll say obj2 sprite dot set texture asset pool dot get texture assets slash images slash blend image 2.png. So we're just refactoring right now, making sure our code works with this new system, which it will, and we'll be good. So then we'll just say obj2 sprite render, and now that should be fine as well. Okay, I'm gonna comment this out real quick too. Let's run this again, and we get everything just as it was before. Cool. So we have now sort of factored that stuff out, abstracted it a little bit, made it better. It no longer requires constructors, which is good. Texture should no longer require constructors too. So this is sort of the last thing that we should do. What we're going to do is, instead of taking in a file path like that, we'll just say public void init, and then we will copy all this stuff. And let's paste it into here. And we will actually take a string file path in here. This is just so that we can, once again, remove these constructors that take in variables. So texture will no longer take that. Now we're going to get an error for this one too. So let's comment that out again, and then we'll get an error inside of our asset pool. So instead of doing this, what we're going to say is texture is a new texture, texture.init, and then we will give it the resource name. So same functionality, just factored out into a different method. Okay. Once again, we get the same thing. This is an image. This is a color. It's all rendering correctly. We're good. Now let's go back to our level editor scene, and let's try and serialize this sprite render for obj2 and obj1 and see what happens. So obj2 sprite render. Let's see what happens when we do this. We're going to get an error. Okay, so we get this giant stack, and you're like, what the heck is happening here? And it's just like, okay, we had a stack overflow is actually what happened right here. So why the heck did that happen? Well, if you look in component has a game object. Let's mark this as transient, because what ends up happening is your serializer is going through and it tries to render this game object. Well, game object just so happens to have a list of components. So then it goes and tries to serialize these components. Well, these components just, and then it goes on and on and on. And that's why we get that stack overflow. So marking this as transient means, hey, we have a circular dependency here. Please do not serialize our game object. We purposely made it that way, but we would like to serialize this part ourselves. So if we run this one more time, you'll notice it runs, and let's see what it printed. Look at that. So it just serialized everything without us having to do a thing. Color is 1111 sprite. It gives us the sprite's path, the texture ID, the width and the height, and the texture chords. This is awesome, guys. If you watch my geometry dash, remember how painful it was to do all that? And now it just literally automatically did it. And we will make this even more powerful too. So just wait. Let's go back into level editor scene real quick. Let's try obj1 sprite, and let's do something interesting. Let's change it from its default. So I'm going to change it to green and move it down here a little bit. Let's see what happens. Well, actually what's going to happen is it's just going to be red anyways because we're doing it right here. But if I take this and we'll just print it out in here, that should not pose too many problems. So we'll create a Gson object in here, and we're just going to get flooded with a bunch of printing messages. And then we will make this obj1 sprite a private variable up here, just for now. And then we'll just remove this just so that we can see and make sure that this is working properly. Okay, so we are going to serialize that every frame, which is slow and stupid, but it doesn't matter. Okay, change the color real quick. Now, if we scroll up, what was the latest color? Look at that. It was whatever we were changing our color to. So not only does this Gson serialize, it can serialize and detect if this sprite render, this color has changed from what we set the default to. Because like I said, it's using reflection, which means that it is dynamically at runtime figuring out what the value is inside this variable and then getting it. Very cool stuff. Very cool. Let's do one more thing. We will try and serialize an entire game object just to see what happens. So I'm going to go up here and copy this Gson object one more time. And we will paste it right up here. And then we'll just say gson.2 or system.out.println gson.2json, and we're going to give it obj1 just to see what happens. So if we serialize this at runtime, what do we get? And let's see if that looks right. So it says name object1 components, and it starts listing off the components: transform, scale, z-index. Cool. So this even works with our game objects, just sort of straight off the bat, goes in and it works. Now, the next cool thing about Gson, and this is going to be where we find our first problem, which we will solve in the next tutorial. But let's take a look at it real quick so that we know what we're dealing with. So let's say string serialized equals gson.2json1. Okay, we're going to serialize that 1. Then we're going to say int 1 equals gson.fromJSON. Then what we're going to give it is just this serialized variable, and we will give it int.class. So the way you deserialize stuff is you say, hey, I want this string to be this class, and then it deserializes it. Then if we system.out.println1, I bet you can imagine what this is going to print out. We'll run that, and we get 1. Cool. What does that tell us? It tells us that this just turned it into a string. Then we just said, give us what this string is, and it figured out, hey, this is a 1. Let's do a little bit more of a complex example, right? Okay, let's try a vector to f. So we'll say new vector to f 1, 1. We'll do 1 and 0.5. Then we'll say vector to f vec equals a gson.fromJSON, and then we'll give it vector2f.class. That's what we're looking for. Then we'll print it out. Let's see what happens here. Okay, we get 1 and 0.5. This is in exponential notation, so that's 0.5. What does this tell us? This tells us we turn this into a string. Okay, remember, we just turned this into a string. Then we literally just said, hey, use this string to give us this class, and it did it. Let's print out that string just so that we can really reiterate what happened there. So if we print out the string beforehand, you'll notice it said, turn this string into this, and it worked. It did that. It's really cool, but now we want to do our game objects, right? Because this is how we're going to do our game levels. We're going to serialize game objects. So let's try that. Let's see what happens. Say obj2, we'll do 1. And then we want to turn that into it. We'll print it out to make sure that it looks right. So we'll say system.out.println serialized. Then we'll say game object obj equals gson.fromJSON, and we're going to give it that serialized again. And we're going to say game object.class. That's what we're trying to cast it to. Now we'll say system.out.println obj.get name. Well, we can't do that. We'll just print out the object, see what happens. But we're going to get this error. What happened here? And let's look here. It's something with our component failed to invoke public j.component with no args. Wait a second. It was trying to invoke component. Component is an abstract class. We should never be trying to invoke its constructor. And this is where our problem lies. So because we have this abstract class, we need to do a little bit of extra work to make sure that this can be serialized correctly and then deserialized to the correct type. So we will talk a little bit more about that in the next tutorial, and we will go over how to solve this problem so that when we go to do this whole serialize, deserialize thing, it will work as you would expect it. In the last episode, what we covered was serialization with Gson. So in this tutorial, of course, we're going to cover deserialization with Gson. That is, we are going to cover how to load text files into our game and convert them to Java objects that are immediately usable within our game. So this will also help out if you're just looking how to use Gson to deserialize abstract data types, because that is the big problem that we are going to run into in this tutorial. We are also going to look at how to create custom deserializers and serializers with Gson to cover this problem. So before we begin coding, let's take a look at the problem in more detail to get a visualization of what exactly we are going to be solving. All right, guys, so the way that Gson works is it uses the class to determine how to deserialize an object. But if you remember, our game object consists of a bag of components, which are this abstract class, which could be one of anything. Any type of functionality you want to implement would be a component. That poses a problem for Gson. How do you know how to deserialize an abstract class, right? Because what we say is, hey, we have a bunch of components, please deserialize this. Then it gets to a rigid body. How does it know it's a rigid body? It can't infer that because currently it's just serializing it as a component. So what we have to do is we have to do a little custom serializer and deserializer for components, because we're like, hey, we need to embed a little bit more information, and it's actually pretty straightforward. It's just like you would expect. We need to say, when you serialize a component, make sure to serialize its type, and we will record that. So if it is a type of rigid body, we will know that. Then we will deserialize it according to whatever that type was. So then when we go to deserialize, we will say, hey, we have a special method that says, look at exactly what type this was, and we will infer this to determine what type we should deserialize it as. Now, this does pose a little bit of another problem, because with Java, you have to have your type names fully classified. So if this is in some sort of package, you would have to list out the entire package name. So it would be like org.commons, whatever, all the way till you get to your components package. And you must make sure that these are all in the same package. If they're not, you're going to run into an error, because then all of a sudden it has no idea what type this is. It needs the fully classified name. That stuff is all fairly straightforward though, right? That's not too much of a big deal. But there was one other thing that we have. So you have game object, you have component. Game object has a list of components. Component has a reference to game object. What do we do about this? So remember, we ran into that Stack Overflow error. It's because when you go to deserialize this, it finds this, then he says, oh, I got to deserialize this, and then it keeps going back and forth forever. So what we did was we marked this as transient, but now what that's saying is just don't even mention whatever this is. But that's not entirely true. We do need this reference. This reference is important, right? So what we can do instead is we leave game object mark as transient. But when we are deserializing a game object, what we will do is we will say, hey, go ahead and deserialize every single component. So then we get a list of components. And as we are deserializing these, let's actually add them to our game object. So instead of leaving the onus on the serializer to figure out how to serialize both of these, we just say, okay, serialize game object. Well, we know we're going to get a list of components with that. Then when we go to deserialize, we go, hey, as we're getting these components, let's add them to the game object, and we gain this circular dependency once again, but we don't run into any Stack Overflow errors because we are doing it once, because we know it only needs to be done once. So this is how we're going to solve these two problems. Just keep it in mind as we're coding, because it is fairly straightforward, but it always helps to have a visualization of what exactly we're doing. So let's actually code this and see how it works. If we take a look at Gson's user guide, we can actually find exactly what we need here. So this is just in case you wanted to try and do this yourself and you're like, how in the world do you even find out about this stuff? Well, look at this. If we check out their user guide, it says custom serialization and deserialization, and then it goes ahead and gives us extensive examples of how to write our own serializers and our own deserializers. And notice these two things. It implements this JSON deserializer, and this implements the JSON serializer with the type of the type you are trying to serialize or deserialize. And then you get a few variables. You get the object in the case of serialization and some other stuff, and then you get the context in the JSON in terms of deserialization. So those are the important things to note about this. Of course, if you have other problems, you can look at other solutions, which I did. So I had a specific problem. I tried to find a better solution than that, and I found it. Now, let's go ahead. We are just going to implement this serialization and deserialization right in here. Probably it would be better in a different class, but for now, this is fine. So what we're going to do is we're going to call this our component deserializer, and this will actually serialize too, but it's fine. And so we're going to say, hey, this implements, and let's take a look at this thing again, the JSON serializer and JSON deserializer. So we're implementing both of these. So we'll say JSON serializer, and we'll give it the component type. And then we'll say it also implements JSON deserializer, the component type. And let's actually just move this to a new line so that we can see all that. Now, if we implement those methods, just hit Alt-Enter to get that to pop up, we get all this stuff. So these are the exact function signatures that we just took a look at. And you'll notice this one throws a JSON parse exception. So this one could actually return a parsing error, which is fine. Now, how do we actually go about doing this? Remember, we said we need to embed the type information when we're serializing. So let's actually serialize first so that we can see how we could do that. What we can do is we can say JSON object result equals a new JSON object. And this is very similar to what Google is doing. Remember, we can look at theirs. They basically say return a new JSON primitive with whatever they're trying to do. We're returning a new JSON object because we have not a primitive, but an object. Then we can say result.add, and we'll say type. This is going to be what type are we dealing with. Then we know this is just going to be a JSON primitive, and we are literally just going to embed the type name as a string. So we'll say new JSON primitive, and we're going to say source, which is the component we're serializing, .get class, .get simple name. You could actually change this to get canonical name, which would reduce the need for having to know the package path, which actually might be a better idea. I think I might do that. So let's see what this is doing too. Right now I'm going to say print line, or actually we'll just print it after we serialize it, see what happens. So we're going to add the type, and then we're going to say we also need the properties, right? And we don't want to write custom things for that because Gson already does all that stuff. So we can just let Gson do all the work for us. We'll say result.add properties. And then we're just going to say context, which is our serialization context, .serialize, source, and then we are going to give it the specific class. So we will say source.getClass. That will serialize the rest of the stuff, and then we can return our result. Now we have what normally would have been serialized, and we have a type, which tells us what type of class we're dealing with. Let's see what actually happens here. Let's go back into our level editor scene, and remember right here, we were serializing stuff, and we tried to deserialize it, which didn't work. Still won't work because we haven't quite finished that part yet. Now, in order to get it to use our custom component deserializer, we have to tell Gson, hey, we're using something special here. And let's see if they actually talk about this too. Yep, so they talk about it right here, right before they do it. And you have to register a type adapter, which basically says, hey, for this class, use this serializer or deserializer, which is exactly what we're doing. So we'll just say inside of this builder, we'll say .register type adapter, and we are registering it for component.class. And the type adapter we want is a new component deserializer. And that will register this to deserialize and serialize our components. And let's go back to level editor scene. Let's just see what happens now. So if we run this, should have serialized game object. And if we take a look inside of our components, we notice it says type components.sprite render. Then it goes into the properties. This is perfect. Now we have our type, right? And let's see if that is the fully qualified class path. That is. So you'll notice it goes all the way down. So we don't even have to worry about what the entire class path is because we're just going to use that. So now that we have the type and the properties, we want to do the opposite, which is to deserialize this stuff. So how do we actually deserialize that? Well, it's very similar. So we want to get our JSON object back. We'll say JSON object equals JSON.get as JSON object. So this is the JSON that was passed in. We're just getting this object that we created back. So we know it's going to have a type and it's going to have a properties. We want to take advantage of that. So we'll say string type equals JSON object.get type, right? It's going to be a type. And then we're going to get it as a string because that is what it is. Then we're going to say JSON element equals JSON object.get properties. This is going to be all of our properties. Next, we want to try and return a deserialized specific component. And so we're going to have to do a try catch because there is an exception that could happen, which is the class not found exception. So we'll say if that happens, we're going to throw a new exception, a new JSON parse exception, because that is the exception we're allowed to throw. And we're going to say unknown element type, and then we're going to say plus type, and we're also going to give it the complete error. And I had a typo there. So we basically throw a JSON parse exception. We don't know what type this is, and we give it the type that we tried to get, which is here, and we give it the rest of the error, which is passed in to that class not found exception. Now, what are we trying to do? We're trying to deserialize a specific class. So what we'll say is return context.deserialize, because we don't want to do this work, element, and we want to do a class dot for name, and we just want to pass it that type. So what this does is it basically says, hey, in this case, we have a components.sprite render, and it's basically saying, like we did in here, we want to do JSON.deserialize, or from JSON, and then it's saying, take the serialized string, and we are doing a sprite render.class. That is all that's happening inside here. We are just doing it a little bit manually because we have to get the type ourselves, and it uses these properties. See, we're saying the element, which is that JSON string, and we are just letting JSON do the work for us. So that's really cool. Let's see how that works out for us. And it's actually still not going to work out correctly because we haven't finished the game object part. So yeah, let's get the game object part done first, and then we'll get the rest of this done. So game object deserializer, we have to do something similar for our component deserializer. We'll go and create a new Java class, say game object deserializer. I guess we should probably call these type adapters, but it's fine. This is going to implement the JSON deserializer, and it's going to take in a game object. We are not implementing the serializer for this because serialization works fine for us. And we get the same method signature. And we also notice this throws the JSON parse exception as well, just in case. So how do we deserialize it? Remember what I said, we basically just have to add the components to the game object as it gets deserialized. So we'll say JSON object equals JSON.get as JSON object. So just like we did. Then we know the string name is going to be JSON object.get name.get as string. How do I know this? Well, JSON is going into our game object, and it's just getting all these properties. So we know we're going to have a name. We know we're going to have a property called components, transform, and z-index. Those are the properties we will get. That's guaranteed. So we're getting those right in here. Now, how do we get that list of components? Well, we can get that as a JSON array. We're going to say is components equals JSON object.get as JSON array, and then we're just going to give it the components name because that was the name of the variable. Then transform equals, and we're going to say context.deserialize JSON object.get, and we know this is called transform, and we're going to say using the transform.class. So that's just like our Gson.fromJSON, except we're saying use this variable name, and that's going to get us the correct JSON, and then we're going to deserialize it to a transform class. Int zIndex, very similar, context.deserialize, JSON object.get, and we're going to say zIndex, and we're just going to give it int.class. Okay, we have everything now, so we can actually construct the game object. We'll say game object equals a new game object, and we can actually pass in the name, the transform, and the zIndex since we have all those. So we'll say name, transform, and zIndex, which is also why we don't actually have to worry about making sure this is constructorless, because we're doing this ourselves. Then we can say for JSON element E in components. JSON array is just an array of elements, and if you remember from our component deserializer, we can literally just do the element and then its class name. But in this case, we don't know what class it is, right? Because this is just a list of components. So what we can say is component C equals context.deserialize E, and we're going to get component.class. So what's going to happen here is the component's going to get deserialized using our custom deserializer, which will deserialize it to the correct subclass, pass it back to here as a generic component, and then we can say go.add component C, which adds the component to our game object, giving us that circular dependency, solving all of our problems. Then we will just return that game object go. So this should solve the rest of our problems. Let's go into here, and we will say, hey, we now want to actually print out what the game object was. So we run it, we get no errors, and we get some random Java address with a j.game object, which means it serialized it correctly, and it serialized it according to all this data. So now we have serialization and deserialization. You may be asking, how the heck do we use this? Like, what good is this anyways? And let's actually find out what good that is. And one more thing too, that probably shouldn't have worked correctly. It actually probably didn't work correctly because we're not using our custom deserializer. So let's actually add that real quick too. We'll say new game object deserializer. And then let's run this one more time, just make sure it works correctly. Okay, still works correctly. Yeah, without this, what would have happened is the game object wouldn't have had any of its components. So we don't want that. We do want to keep the components. So let's implement a saver/loader with this real quick. And just as a side note, if you remember my Geometry Dash series, this took 40 minutes for each episode on serialization, deserialization. And then I don't even remember how long the saving and loading files came. So yeah, this is great. Let's go into our scene class. I'm going to copy all this too and just remove it. We will go into our scene class and we're going to create a couple of methods. One of them, public void load. Let's paste all that in there real quick too. And I'm just going to take out these print lines. We don't actually need this. We just need the Gson object that we will be using. And one last thing. Well, we'll save that for later. So what we're going to do is we're just going to do it very simply for now. We're just going to say string in file, which is whatever file it's getting it in from. And we'll do the export first because that will probably make this a little bit easier. So I'm going to say save exit, which basically means save a file and exit. We are going to use this Gson object. And what we're going to do is we're going to try to write a file, and we will catch an IO exception, E, just in case, and then we'll just print that stack trace. Should be good. Then we are literally just going to do a file writer, say writer equals a new file writer, and we're going to say level.txt. You can change the file format too, and actually zip it up and everything, which we might do in the future, because that's probably better. Then we're going to say writer.write gson.to JSON this.gameObjects writer.close. That is it. We are now saving our entire file with this tiny function. Okay, this is amazing. This is so much easier than what we had to do in the past. Now, deserialization, almost just as simple. And what just happened here too, we literally just wrote the file. We said, write out our game objects, which returns like this big array of game objects, and it just turns it into JSON perfectly fine, which is technically JSON, without any other hassle. That's awesome. Okay, let's go and read it back in. So we'll say try in file equals new string files.read all bytes, and we just want to read paths.get level.txt is what I called it. So this is just a very simple way to read a file into a string in Java. So we're literally just reading all the bytes. I think you could have problems with this if your files are too large. It's actually going to truncate it, which is not good. So we will look into that in the future too. But let's say if not in file dot equals empty quotations, so the in file worked, and then we're going to say game object objs equals Gson dot from JSON. We're going to give it the file that we just read, and then we're going to say game object dot class. Actually, I think it's game object array dot class. So we're reading in a game object array. Then we can say for int I equals 0 until I is less than that array's length, I plus plus. We will add game object to scene, and we're going to say obj's I, which should add that game object to the scene. And then we're also going to set a flag to true. This will help us so that we don't reload levels if we don't need to. So let's go in here, say protected level loaded equals false initially, and this is a boolean. But if we load a level, then we will set this dot loaded level, or level loaded is true. This will just help us prevent us from shooting yourselves in the foot and reloading a level multiple times when you don't need to. So like we actually create a level here, but we don't want to reload that. So I'm going to keep these two lines. I'm going to say if level loaded return. Otherwise, we will actually create the level. Now, let's see what happens. So if we start this up, we get this. I'm going to change this to blue. Close it and start it back up again. Nothing's going to happen. So that was kind of anticlimactic. We still have to hook those functions up, which I forgot about. So we have the load, we have the save exit function, but we're not actually calling them. Let's go into our window class. And very simply, what we're going to do is we're going to say right before we start this loop, we're going to say current scene.load, and right after we finish the loop, we're going to say current scene.saveExit. Okay, so now we call those functions when it would be appropriate. Let's change it again. Exit. You'll notice it says an external file was added. Let's see what happens when we run it. We get a blue and a green object. So this actually worked, guys. Let's take a look inside of our folder. So if we take a look inside of our folder, we'll see we get this level.txt. And if we open this up, we get this object1, tells us the components, the fully classified type name, the properties. Then we get the transform, the z-index. We get the next object, we get its components, and everything. So you'll notice it's actually serializing them twice too. We got a copy, which that's not good because that means we're adding it. And actually, I think that's because we're actually adding this twice. Let's go into here. Okay, so that seems to have been a bug when we loaded it twice. So I just deleted the file and then redid it, and we just get two objects. Let's run this one more time. So this is a good intro to bug testing too, to make sure that you don't have any unintended bugs. You'll also notice that this is no longer the active game object. We could fix that, of course, real quick. Let's just make sure if we run this a couple more times though, that the file doesn't start growing. And it does start growing. So this is definitely a problem. We don't want to create copies of these objects. So that is something that we'll take a look at in the next tutorial. But we are saving and loading the data, which is a huge step. And we'll take a look at that bug in the next tutorial, and we will also take a look at dynamically generating some ImGui property windows for these game objects using reflection. In the last episode, what we did was loading levels with Gson. We encountered a bug at the end of that tutorial, but we will be solving that first thing in this tutorial. And we will also be doing something super cool, which I am really excited about because we will be exposing variables to the editor through the use of reflection. This is just like Unity does, and it saves us a ton of hassle and makes everything so much nicer. And it's just a really cool feature to have if you're making your own engine or level editor or anything. So we will take a look at how that works, and then we will implement it, and we will also fix that bug. All right, let's get started. All right, so before we actually start coding, I do want to formalize the exact problem that we are trying to solve. So inside of your game world, you will have several components that look something like this. And within these components, you will have several fields, is what they're called, that look like this. So these are your private and public member variables to this class. Now, usually you want to save these fields. Well, not usually, you always want to save these fields for a level because you want your initial starting point to always remain the same. So how do we go about exposing these to ImGui so that we can change them and save them easily, right? Because we want to change these in an easy to use manner. We want an ImGui window to pop up that reflects this exactly, where it basically has a box that's like, this is your friction, and then you can change it here, and then you have another box that's like, this is your velocity, and you can change this here, and so on and so forth. And the red is public and the blue is private. I differentiated that because, you know, sometimes you might want to differentiate that too. So what we can do is we can use Java's reflection, and Java's reflection allows us to say something like get fields on a class, and what this does is it returns all of these member variables: public, private, protected, transient, everything. It gives us everything. We can check whether it's public or private and do all that type of stuff, which I'll show you how to in case you want to. But the other cool thing we can do is we can find out what type each of these are. And since we have a limited number of types that are really going to be exposed, a limited number that we can have, we can actually create a function for the most common types, and it will cover all those. And then if you need to do something a little bit more complex, we can let the user decide how to do that. So we'll take a look at how to start doing this automatically by creating one sort of God function that basically creates all of the ImGui windows that we may need. And then we can add functionality to this as we see fit in the future, or we can just create custom ones for specific components. And I'll show you how we can do both of those in this video. So let's take a look at how to get those fields and then start creating an actual ImGui window for all our components. So the best place to put this whole functionality, of course, is going to be inside of our abstract component class. What we're going to do is we're going to implement this ImGui function, and it can be overridden if any of the classes inheriting this would like to do so. Basically, what we're going to be doing is exactly what I said. We're going to be getting those fields. So we have to wrap this in a try-catch because there is something that could happen, which is called an illegal access exception. And we're just going to say e.print stack trace. Basically, what that means is you just try to get a member variable that doesn't exist. We don't have to worry about that too much because we will not actually be getting anything that is not explicitly in the class anyways. So next, what we're going to say is field, and I'm going to import that from Java's reflect. Fields equals this dot get class dot get declared fields. What this is going to do is it's going to get it from whatever subclass is currently running this component. So it's not going to be doing it on component, but if it was a rigid body, it would be doing rigid bodies class get declared fields, which would get all of these fields for us. Then what we can say is for field in fields, we'll do a loop, and then we will basically start to do the part which is building the ImGui window for each field. So what we have to do is we have to first figure out the type. So we'll say the type is this current field's type. So this would be like if we were on this first one, it would be like the type is game object. Then the object or the value is just the field.get this. This is the way you get the actual value contained within that field using reflection. And then we would say string name equals field.get name. And so the name is just going to be whatever this is. So whatever you named it. So game object would be the name of this one. And then the object would be null for this, since that is the value currently contained within that field. Next, we can just simply start creating a bunch of different cases. So we'll say if type equals int.class. And also, in this case, I would usually do a switch statement, but you can't do a switch statement with class comparisons. So we're just going to stick with a type because it's just simplest. What we can do now is we'll say int val equals, and we're going to cast this to an integer, the value that we got, so that we have it as an integer. Then we're going to say int array ImInt equals val, because ImGui expects an array for an integer. And then we'll give it a drag int. So we'll say if ImGui.drag int name plus colon, and then we're going to give it that ImInt. And then we'll say field.set this ImInt 0. So what the heck did I just do here? I said if, and then I gave it the ImGui that we are working with. So this is a drag integer where you drag an integer. Then the label we gave it is the name. So that would be like game object colon. And then the value I gave it was whatever the current value is. Then if this changes, we set the field to whatever that changed variable would be. So let's see a concrete example of this. Let's create a new component that will sort of be our test component. We'll just call this rigid body because they have lots of easy to use variables that everyone uses all the time. Okay. So we say that extends component. Then what we're going to do is we're just going to give ourselves a few variables. So we're going to have a public integer. We'll call this collider type, and then we'll initialize this to 0. And we'll say public. Actually, and let's not make these public. Let's make these private, just so that you can see that this will still work. And then we'll do a private float friction equals 0.8f. Then we'll do a public vector 3f velocity equals, and we'll initialize this to 0, 0.5f, 0. And then we'll do one more transient one. We'll say public transient. And this will be vector 4f equals a new vector 4f 0, 0, 0, 0. And it's not going to be called vector 4f, it's going to be called our temporary variable. So this is the variable we just don't want to show up, which is how we'll decide that for now. Now let's go into our level editor scene, and let's actually add this component to this guy. We'll just say obj1 to add component, and we'll say new rigid body. And we'll check and see what happens. So nothing's going to happen because of that bug. Okay, I said we would figure out that bug real quick. Let's actually figure out that bug, and then we also get an illegal cast exception. So, okay, so first let's solve that bug real quick. So if we go into our window class, we did current scene.load right here, and I actually have a to-do in here because I did look at it right after I finished that video. And we save it right here. So what's happening? Why are we getting that duplication error? Well, I say move this into the change scene function to fix duplication bug. How is that going to fix it? So if we go into change scene, which is up here, what we do is we say current scene equals new scene, then we say current scene.init. Well, what happens in init? Well, in the case of level editor scene, we check and see if the level was loaded. If it was, we return. Well, the level is not going to be loaded yet, right? Because we actually load it right down here, which is right before we start the loop. And when do we start the loop? We start the loop right after we change the scene completely. So that gets called, then this gets called, so we actually create those and then we double create them by calling that. So I'm going to copy and paste this, and we will just say paste it instead right up here, right before we do the init. And then we'll do the same thing here. And we could actually too just do this. I do want to eventually switch this to, instead of doing a number, to just have them pass in the scene. That way it's more flexible. And then we could get rid of all of this, and then we could just do everything down here. But anyways, yeah, so that should fix the duplication bug. So let's try this again, and then we're getting another bug down there, which I will talk about in just a second. So we get nothing. And the reason we get nothing is because of another thing that we have to worry about. So sprite render. So the reason we're not seeing them is because we had isDirty set to false, and so they were never being told to update, which means we never actually saw them. So if we just initialize isDirty to true, then we get them, and then we get an error with our texture. So that's just another thing that we'll have to worry about. But I'm going to save that for later because right now we are worrying about exposing these to the level editor. So let's go back into here, and we will make our active game object. If the level is loaded, we'll say is equal to gameObjects.get 0. So we'll just get the 0th game object and get that. Okay. Now we have this game object as our active game object again. But you'll notice we're getting this error now, which is saying it's because we're trying to access a private member. So if we look, it says this field is private. So what we can do is we'll first of all set boolean is private equal to, and then we'll say modifiers dot is private. And then we'll say field dot get modifiers. So this is how we can check and see if something is private. And then you can also check and see if it's protected and so on and so forth. We'll say if is private, and then we want to set it so that we can actually access this field. So we'll say field dot set accessible true. Then we will go ahead and do everything. And then after we finish, we'll say if is private field dot set accessible false. So basically what we're doing here is we're temporarily changing it to a public field, and then as soon as we finish with this, we're sending it to a non-public field. So if we do this again, you'll notice we can now access this. I'm going to change that to 10, and we get no errors. And then if we reload this, you'll notice it has saved the new value. So what we have done there, we just exposed that variable to our editor, right? So we have this thing called collider type, and it was set to 0, and we exposed it. So now we just have to go ahead and do the same thing for friction, velocity, and this temp variable. We should make it, because I'm going to use transient as a keyword. That means we cannot expose it. So let's go ahead and get those last things up too. And it's actually exactly as you would think. We'll just do something like else if type equals float dot class, say int. Actually, this is going to be a float now. Float val equals float value. Then we'll say float array float equals val. And we'll say if ImGui.drag float. And we gave it the name plus a semicolon. And float. Then we'll say field.set this float 0. So same thing. That's floats done. Now let's do else if type equals bool in .class. I've been coding in C++. It's bool in C++. So we'll say boolean val equals boolean value. And then we'll say boolean array bool equals val. Then we'll say if ImGui dot checkbox. So we'll just give it a checkbox. And actually, we don't even need to do the array thing too. We'll just say name plus colon, and then we'll pass it the value. So we can actually just take that part out. And then we'll say if it was checked or unchecked, then we'll just say val equals not val. So that one's actually pretty simple. We can just change it. Actually, we'll do set. So we'll say field.set this, and then we'll give it the value. Actually, no, we should do val equals not val. Okay, because otherwise, if we don't, it's not actually changing this value, and so we actually need to change it ourselves. So we do this, and then we say field.set this to val, or more concisely, like that. Okay, sorry about that. Now, let's do a vector3 real quick. We'll say else if type equals vector3f.class. We will do a vector3f array. So first of all, we'll say vector3f val equals vector3f value. And then we will say float ImVec equals, and then we'll give it the val.x, val.y, and val.z. Then we'll say if ImGui.drag float 3, and we'll give it that ImVec, or actually we have to give it a name first. So we'll say name plus colon, and then we'll give it the ImVec. Then we will say val.set. Actually, we'll say field. Yeah, we'll do val.set first. And then we'll say ImVec 0, ImVec 1, ImVec 2. And this one should actually change the field too. So like, because these work different, these are different than primitive types. So if you change one of these, you're actually changing the actual object. Whereas if you change a primitive type, you have to say field.set because you're not actually changing the primitive. You're literally just copying that value. So difference between those, which is why we're doing this. Let's run this real quick. We should see the other parts of our fields popping up. So if I make this bigger, you'll notice we have collider type, we have friction, we have velocity, and they all have the initial values that we had, which is really cool too. But if I change them, and then I exit, and then I go back in, it saved the values that I got, which is super cool. So we are now exposing these to our editor. Let's go ahead and also say vector4, because this way we can actually implement that transient keyword. So we'll say else if it's a vector4 f.class. I'm just going to copy this because it is very similar. Change this to vector4f instead. Change this to vector4f. And then we will also give it val.w. And then we will also set it to imvec3. And we will change this to a drag float 4. Okay, so that should be good for vector4f. And then what we're going to notice is we actually get this temp variable in here. We don't want it to be in there because we marked it as transient. So what we can do is, just like we did for our private, up at the top we'll say boolean is transient equals modifier dot is transient. Then we'll get field dot get modifiers. Then we can say if is transient continue. We'll just skip over all the transient variables. That way we have a way to mark things that we don't want exposed in our editor, which is nice. So now if we run this again, temp is now gone, but we have all the other variables, and if we change them, we save the values. This is a huge, huge step in getting our level editor done. Now that we have a way to do this, where we can literally just add it in one place and it adds it for every single component, building our level editor will be really nice and easy. So what's up with this texture too, you might ask? I think I know what the problem is. If we go into our level editor scene, we load the resources, but what doesn't get loaded, blend image 2, does not get loaded. So what we should actually do is just copy this, paste it right here, and let's see if that fixes it. I'm not sure if this will. Okay, so it fixed it, but I'm using the wrong image there. So something clearly happened. Okay, so what happened here? What I'm going to take a guess at so that we can fix this in the next tutorial. Notice how it's a completely different texture. I think what happened is because of the order we're loading things. Okay, so in here we load this first, then we load this. Whereas down here we load this first, then this. So if I move this down, I think it's going to fix that issue. Okay, and it fixes that issue, but I'm going to say that's definitely not the behavior we want. So we're going to have to relook at our asset pool and make sure that when somebody, or actually we can just relook at how we're building textures, and then we can look for, see if we have the texture available and everything, and figure stuff out that way when we're loading stuff in. Yeah, so we'll take a look at that, because right now what it's doing is it's doing it based on the ID. So this would be 0, 1, and then if we swap them, now all of a sudden this is 0, this is 1. And because of the way we save the data, we only save the ID. So then all of a sudden it's taking this sprite sheet instead. So that is the problem. And we will take a look at how to solve that in the next tutorial. But yeah, I hope you guys like this. This is, like I said, a huge step to fixing or completing our level editor. In the next tutorial, what I plan on doing is expanding our level editor so that we can actually start hopefully maybe dragging and dropping stuff in and placing them in the scene. If not that, we will be definitely building like the things specific to level editor scene. So we will actually be building a window that is specific to our level editor that will allow us to begin doing the drag and drop stuff. So in the last episode, what we did was we got our variables exposed to the level editor. So that's a huge step, and it allows us to start the next step, which is to actually start building levels. So what we're going to be doing in this episode is actually building a menu where we can click onto different items and we can tell which item we clicked on. And then we're also going to start doing a screen coordinates to world coordinates conversion. So we're going to look at how we can do that, and then we're going to get both of those things done. So you should see a little bit of something of what we're working towards in the preview above, and that is what we will be working towards in the next few tutorials. Okay guys, so without further ado, let's get started. Okay, so the first thing we're going to take a look at is how we can get our icons in our menu to do something like this. So ImGui does not natively provide a way so that if you resize the window to the left and the right, the icons will resize with the window. You have to do that manually, but I will provide a link in the description where the creator of ImGui has actually just shown you how to do it. It's pretty simple if you just think about it. So we're just going to draw it out so you guys know exactly what we're doing when we start to code. Basically, what we have to do is we have to first get a hold of the Windows X2. So the Windows X2 is this point right here. Then, as we start placing icons onto the window, what we do is we get a hold of this point, and we get a hold of this point. We can get a hold of this point if we know this point. So we'll call this point our last X2, and then we'll call this point our next X2. Okay, and so what we're going to be doing is we're going to be iterating through all the icons we want to be up here, which is basically just all the images in our sprite, right? So we'll be starting from here. When we're on this iteration of an icon, we will be getting a hold of this X2, and we'll be getting a hold of the next X2. Then when we move to here, this will be the last X2, this will be the next X2, and we continue to do that. And then what we'll do is we'll say once we get to here, we would be right here, and this would be last X2, and next X2 would be somewhere out here. And so we'll say if next X2 is greater than window X2, and you could do greater than or equal, it just depends on your preference, then we go to new line. So we'll say next line please, and we'll just use ImGui's functions to get all this functionality that we want. And then this will ensure that our icons will just readjust accordingly. And we'll be building this every frame, so it's fine that we have it this way, because basically if this resizes, window X2 will change, and then we can, once again, we'll be running this loop again, and then all of them will adjust dynamically. Okay, so it's not too hard to understand. It's just nice to have a visualization of what exactly we're going to be doing. The next part is a bit trickier. So this was really difficult for me the first time I did this, but it doesn't have to be. It's actually quite simple once you know the math behind it. Okay, so I have a picture of a screen here. The screen's actual width is 1920, its actual height is 1080, and we have its projected width. So this is just like pretend. So pretend its projected width is 1280, its projected height is 720. So that's the world width, and the world height, you could say that's visible on this window. Then we have a camera X, right? Say the camera X is at 500, the camera Y is at 20. So in world coordinates, this bottom left point is actually at 520, but in screen coordinates, it's at 0, 0. At world coordinates, this bottom right corner is 1780, 790, I think that is. No, that should be 740, maybe. And then in screen coordinates, this is 1920 by 1080. How do we convert from these screen coordinates to these world coordinates? And that can be a little bit tricky if you don't know how to think about it. So I Googled a lot and I found some different answers, and then I found the one that I thought was the most appropriate. So if you remember in our shaders, what we do is we say GL position equals our projection times our view times our A pose. What is this? Let's just get a little refresher. Projection. The projection is just this stuff. It's how big we want the screen width to actually be. The view, what is that? That's just our camera position, our camera orientation, all that stuff. What is A pose? Well, that's like the actual position of the world, the objects in world space. So that would be like these actual specific coordinates. GL position, what is that? That's a normalized device coordinate. That means it's a screen coordinate ranging from -1 to 1. You may be thinking, how the heck does this help us at all in this situation? None of these translate back to 1920 by 1080, but one of them does translate back to 1920 by 1080. This -1 to 1, we can get very easily from this 1920 and this 1080. So basically, in normalized device coordinates, this left corner would be -1, this right corner would be +1, this bottom corner would be -1, this top corner would be +1. These might be flipped in OpenGL, I'm not sure. But the gist of it remains the same. You have the -1, you have the +1, and you need to get from 1080 to this, right? From 0 to 1080 to -1 to 1, and then same here. That's not too hard to do, right? So if you have a point in your screen, say right here, how do you get that in range of -1 to 1? Well, you would just say, okay, it's x, y. If we divide that, so first we say x divided by 1920, which is the total width that you could have, and you say y divided by 1080, which is the total height that it could have. This will normalize it. This will get it in a range of 0 to 1. Now, that's not -1 to 1, but it's close. So then to do the next thing, all you would have to do is you would have to say multiply these by 2, subtract 1, and that should normalize it so that it is now in a range of -1 to 1. And if you think about this, this will always work. So say this is 1920, that would be 1. Say this is 1080, that would be 1. So 1, 1 times 2 is 2. -1, you get 1. Say these are 0. 0, 0 times 2 is 0. -1, -1. And then you get everything else in between. So this is our conversion factor to get from 1920, 1080 to -1 to 1. So then how do we use that information? Well, we have a direct mapping right here, right? So this is world coordinates. This is -1 to 1 coordinates. We just do the reverse of this. So if we want to get world coordinates equals from here, you would say, well, this is GL position times inverse projection times inverse view. Those inverses are important because we can't just say 1 over P. If you're thinking in terms of numbers, you would be like, oh, if I have 10, the opposite of 10, the inverse of 10 is 1 over 10. That's true, but in matrices, the inverse is not 1 over the matrix. So we have to be very careful in our wording here. We can't just do 1 over P and 1 over V. We have to do something different. But basically, all the inverses too is just the reverse. So what we're saying is we want to reverse what we did. We want to go from GL position to reverse to reverse. So we take this -1 to 1 coordinate, multiply it by P inverse, multiply that by V inverse, and we get our world coordinates, and that works perfectly. So as we're coding this, I'll sort of show you the different steps too, just so that you can prove to yourself that it all works like you would think. But that should cover it. Let's actually get started, and we'll do the first part, which is the icons, and then we will do our mouse projection coordinate thingies next. Okay, so I'm inside of our level editor scene here. Let's just run this one more time so that we can get a visual representation of where we left off. There we go. So we just had an ImGui window, and we have our little color picker and everything, and we have this test window, which currently does nothing. Just gonna move these over a little bit. Okay, I have a to-do in here too. So remember, the texture was broken. These to-dos are helpful because it reminds me we need to fix it. We'll save this for now, but we will get around to it eventually. Now, let's go into our ImGui. So this is where we're going to be creating those icons because we want to create it inside of the ImGui window. First of all, let's actually make sure we're always creating the sprites. So let's make sure we are always loading the sprite sheet just in case, because if we're not, we'll get a null pointer exception when we go down to here. And I'm actually going to change the sprite sheet too. So currently we're using just a standard sprite sheet thingy. So we're currently using like character sprites. I'm actually going to use this sprite sheet right here, which is the decorations and blocks inside images. You can get this off of my GitHub if you want to, or you can just use whatever sprite sheet you want. So I'm going to go images, assets, images, and then sprite sheets, and decorations and blocks. And then I'm also going to go down here and fix this loading. So this is actually in sprite sheets / decorations and blocks. Copy that, and we'll just add an S there. Do that one more time. They have the same width and height, the same spacing, but we now have 81 sprites. So that should be good. We should be loading the correct sprite sheet now. Now, if we actually go to build the window, this is literally taken straight from the link in the description. So what he says to do is first get the window position. In Java, it's a little bit more annoying than in C++ because we cannot pass around references easily. So we'll say get the window pose and store it inside of this variable we just created called window pose. And that will get the current position of the window. Then we're going to say ImVec2 get window size. So we want to get the window size too. And then we want to say ImGui.get window size and put it inside of that window size. And that should be new. Then we will say get the item spacing, because that is something else we will need, and put it inside of this variable item spacing. So we'll say ImGui.getStyle.get item spacing and put it inside of there. Next, we will calculate x2. So Windows x2 we can now calculate, which is just the Windows position.x plus the Windows size.x. So that is the rightmost coordinate of the window on the screen. Then we'll say for int I equals 0 until I is less than sprites.size. Let's create that function real quick, and we'll say I++. Let's go into our sprite sheet, just add a function really quickly. Say public int size return sprite.size. Go back into level editor scene. And now as we're looping through the icons, we can do our little place the image and then put it on a new line if we need to. So we'll say sprite equals sprites.get sprite I, and we do need to get a few things from it. So we need to get its width, its height, its texture ID, and its texture coordinates. So we'll say float sprite width equals sprite, and we may have to create these functions, which we will do in a second. And then we'll say float sprite height. And these aren't like the actual sprite's height. This is going to be the width and height we want it to be. We'll say sprite.get height times 4. And then we'll say int id equals sprite.get text id. And then vector 2f text chords. This one we actually do have done. So let's say sprite.get text chords. Now let's create these functions real quick. Shouldn't take too long at all. So we'll go into sprite, and I don't think it currently has. Let's remove this too. We no longer need these constructors. Let's put private int width and height, or actually let's make these floats, width and height. Then we will go down here, create getters and setters, and actually somebody told me there is a way to generate these functions, which I will try real quick. So if we go to code and then generate, we'll say getter and setter, and we'll do both of these. So we'll say width and height, okay. Well, that's pretty cool. So thank you for whoever shouted that out. I can't remember, I'm sorry. But now we can have those generated automatically. Okay, let's go into the sprite sheet now because we do want to set the width and the height as we are creating these. So when we're creating it, we'll say sprite.setWidth, and then we'll give it the sprite width and sprite dot, this is inside sprite sheet too, by the way, sprite height. Because we're getting the sprite width and sprite height here. These are uniform, and then we just set them here so that we know what it is. And we do also want to create a text ID. So back into sprite, and we can actually just go down here. We'll just say public int get text ID, return texture equals null. If it's null, then we'll return -1. Otherwise, we'll return texture.get ID. And let's go into texture real quick and just create a getter for that. And we have the text ID. We just need to create the getter. So we'll say public int get ID, and then we'll return text ID. There we go. So now we should be good. We got all of these done. Next, we actually want to place these onto our ImGui window. So we'll say if ImGui.image button, which is exactly what we need. It takes in a texture ID. Well, we just got that, the ID. It takes in a size for the X. Well, that's the size you want it to appear on the screen, and the height you want it to appear on the screen. Now, UV0, X, and Y determine what size it actually is on the texture. So we'll use our text chords, 0.x, text chords, 0.y, and then we'll use text chords 2.x and text chords 2.y to get all of those done for us. And that should be good. This is a long statement. Take a look at it real quick. And then I'm going to open up my brackets for that if statement. For now, we will just say system.out.println button, and then we'll say +i plus clicked. And let's go ahead and calculate whether we want the next one to be on the same line or not. So we'll say ImVec2 last button pose. So this is the last x2 type thing. We'll say new ImVec2 ImGui.get item rect max, and then we'll give it last button pose. This will get the last button's position, which is actually the button we just created. We'll say float last button x2 equals last button pose.x. Then we'll say float next button x2 equals last button x2 plus item spacing dot x plus sprite width. And that will get us the next position for the next x2. Then we can say if I plus 1 is less than sprites dot size and next button's x2 is less than Windows x2, we want to place the next button on the same line. So we'll say ImGui.sameLine, and what this does is it will place the next item on the same line as the current item. So next time we run this, it will be on the same line as the previous image button that we created. Okay, and that should be good. Let's run this, see what happens. We should get some buttons. And look at that. We get buttons, and you'll notice they resize. But I'm going to click here, click here, click here. We should have gotten 3 button clicks, but watch what happens. We get button 0 clicked, nothing else. Why did that happen? So you might be confused at first if this happens, but it's perfectly fine. The reason this is happening is because ImGui uses an ID system, and it uses IDs to determine if something's clicked or not. The ID it uses in the case of an image, however, is its texture ID, and these all have the same texture ID because they're part of a sprite sheet. So what we have to do is say give each of these a custom ID. So we'll say push ID, and we'll just give it the index they're at, which is I. And you don't have to worry about this clashing with other windows because the IDs are just according to a single window. So since we're making one window in here, we can use I and be perfectly fine with that. And then we'll say ImGui.pop ID. And what that will do is it'll give the button the ID that we just placed in here. Now if we run this again, and we click here, then here, then here, you'll notice we get button 0, button 11, button 36. Cool. So that's the first half of our thing done, right? We have a resizable window that actually detects when we click things. Next thing we have to do, because this is going to be important for our next tutorial when we actually start to drag and drop things, is fix up our mouse listener so that we can get some screen to world coordinates. So let's go to our mouse listener. And we will go down here right below get X and get Y. We'll say public static float get ortho X. And we'll do public static float get ortho Y. And before we can actually implement these, we have to go to our camera because we do need a couple more things. So we have projection matrix, we have view matrix. Let's also add in inverse projection and inverse view. Now when we go into here, we want to initialize these. So we'll say this dot inverse projection equals an empty matrix 4F. This dot inverse view equals an empty matrix 4F. That's cool. Every time we do an adjust projection, we would like to say projection matrix dot invert into our inverse projection. So this will invert our projection matrix and put it inside of here. Every time we do a view matrix, we would like to do this dot view matrix dot invert into our inverse view. Once again, we'll invert our view matrix into this matrix. Then we want to create a couple getters for these. So we'll say matrix 4F get inverse projection, return this dot inverse projection, public matrix 4F get inverse view, return this dot inverse view. All right, so let's go back to our mouse listener and actually implement that thing we talked about. So first thing we're going to do is say float current X equals get X. And I'm going to return -1 here too so that we don't get any errors for now. Then we're going to say current X equals current X over float window.getWidth. So that should convert it to a 0 to 1 range. Let's actually just print this out real quick, just so that we know this is working. So we'll say print line. I'm going to go to my level editor scene, and we're just going to say inside of our update method, mouse listener dot ortho X, get ortho X. So let's run this, and then gonna make my window a little bit smaller. So if I move my mouse over here, we should be getting something like 0, and then if I move it over to here, we should be getting something like 1. And we're getting nothing. Did I forget to print it? Oh, yeah, it would help if we're actually printing the values. So let's print current X, okay? And then we'll run that one more time. So if I go over here, we get 0. If I move my mouse to the right, we get something very close to 1. Okay, so that part works. Now, like I said, if we multiply this by 2 and subtract 1, it should convert it to -1 to 1 range. So let's see if that's working. So if I move my mouse to here, we get -0.9, very close to -1. 0.99, very close to 1. Okay, so that part's working too. Next part. We're going to create a temporary vector 4F, a new vector 4F. We're going to give it current X, 0, 0, and 1. Do not forget that 1. It is important to maintain the integrity of our matrix multiplications. So we need a vector 4F too, because you can't multiply a matrix 4F by a float. You have to multiply it by a vector 4F. So we'll say temp.multiply window.getScene.getCamera or camera dot get inverse projection dot multiply window dot get scene dot camera dot get inverse view. And what is this going to do? It's going to sort of undo all the operations to get it to screen coordinates, right? So now we should be getting world coordinates for our current X. Let's run this one more time, see what we get, see if it looks like something we would believe. So if we go to the left, we get -1. That's because we never actually changed current X. Let's change current X here. We'll say current X equals temp.x so that we actually set it to the new value. And then if we go back into here and we move our mouse to the left, we get -212. And to the right, we get 1030. That sounds right to me. Let's just double check. Level editor scene. The camera starts off at -250. And if we look at the camera's width is 32 times 40. So we should be getting -250 and then -250 plus whatever 32 times 40 is. So 1030, I believe, is what that is. And then we were getting -212. Let's run this one more time just to make sure. So if we run this one more time and we get really close to the left there. Okay, yeah, so it's -248. This is working good. So now we're getting world coordinates, okay? That's not too bad, right? This took me like hours the first time, and I don't even know what I was doing, honestly. It was not correct, though. So yeah, this is the correct way to do it, and it's actually not that bad. Let's just copy this and do the same thing for our Y. So we'll just change this to current Y, not T, current Y. Change this to current Y, that to 0, and make sure you actually put it in the Y direction this time. So Y equals, and we want to make sure we do Y. Okay, and that should be it. So now we have a way to get mouse coordinates in world coordinates. So since this is done, in the next tutorial what we can do is we can actually start getting around to clicking these and dragging some object that is this into our world. And then I also want to get into mouse picking, which means we'll be able to like click on this, and then our inspector will be inspecting this object. And if we have more objects, we can click on them. Inspector will inspect those objects. All right, that has been it for this tutorial, though. I hope you guys liked it. If you did, please hit like and subscribe so that you can get notified of when we do the next tutorials. In the last episode, what we did was we created a level editor, or we started creating it, and we got blocks up on the screen that we can select from. However, we can't actually drag those into the scene yet. So in this tutorial, what we're going to be doing is implementing that functionality, and we're also going to be creating a global ID system. This global ID system is a little bit of future proofing so that when we go to save and deserialize levels, so save and load levels, we will not be messing things up when we store references to other game objects and components inside of our component classes. So yeah, I'm going to explain how all this works, and then we're going to implement it, and let's go and do that real quick. Okay, so we're actually going to do a few things today. First thing we're going to do is fix this. So in the last tutorial, I made a mistake inside mouse listener. Inside of the get ortho Y function, it should be get height, not get width. So let's fix that up real quick. Go into here and literally just going to change this to get height. And back in the level editor scene, we are going to start beginning our next part of the project, which is whenever they click a button inside of here, what we actually want to happen is for them to pick up, quote unquote, the object. So what we're going to do is create a couple new classes to help us out with that. And while we're at this too, let's start fixing things up just a little bit more. It's getting kind of messy inside of our editor over here, and I like it to be a little bit more organized. So I'm going to move component over to here, hit refactor. I'm also going to move component deserializer into components and hit refactor. Next, I'm going to create a new package inside of here. We're going to call this one scenes. So we'll hit new Java package, and then just going to call this scenes. We're going to move scene into here, and we are going to move level editor scene, and we're going to move level scene. So get those all out of there, because what should be in Jade is really just like the core engine features. Yeah, and that should be good for now. Let's just run it one more time just to make sure that we didn't break anything by refactoring everything like that. All right, and it's still working okay. We can click on these and everything and nothing changes. We get the button clicks. So that's all good. Now let's go into here. We're going to create a new class and we're just going to call this prefabs. This is kind of my idea of prefabs in code. It's a little bit weird, but it's helpful when you're creating a lot of objects that have the same general layout, which is what we're going to be doing. When we click on one of those pictures, what we want to do is we want to basically create a game object that has that sprite, right? So we'll say generate sprite object. And what we're going to take in is a sprite, and we also want to know the size in the X and the Y. So we'll say int size X, int size Y. So we want to know how big it is and what sprite they want to use. Then inside of here, what we're going to do is we're just going to say game object block equals new game object sprite object, and I'm going to do gen just so that we know that this was generated. And for the transform, we're going to give it a 0 position and size X, size Y, and a 0 index. So we'll just say new transform. And I'll move this to the new line too, just so that we can see this. And Control P to bring up those parameters. Then we'll say new vector 2f, and we'll say new vector 2f, size X and size Y. Oh, and we need the Z index. So then don't forget that 0 Z index. Okay, and then what we're going to do is we're going to create a sprite render. This is sort of like what we're doing inside of testing, except we're just sort of automating that process. Say that's a new sprite render. And then we'll say render.setSprite, and we will give it the sprite that was passed in. And then we will just say block.addComponent that render. And then we'll return the block. So this will generate a sprite object with whatever sprite you pass it in, which is kind of nice. In the future, I do want to have this fully automatic so that you can do all this in the level editor. But for now, we're going to do a function just to make things a little bit easier on ourselves. Now, if we go back into our level editor scene, there's going to be a couple things that we will want to do. So this is now in scenes. When we click on one of those objects inside the ImGui window, right? What we want to do is we want to first generate one of those blocks, right? So that part's easy. We just say game object equals, and then we'll say prefabs dot generate sprite object, and we will literally just give it the sprite, and we'll give it the sprite width and the sprite height. So that's the same size that we gave it, and we can modify those later on if we want to and all that stuff. So, and we're just gonna have to cast these to integers just so that's happy. Actually, you know, let's change the parameters here so that this takes in a float, because that makes more sense anyway since we're making these vector 2f's. So yep, those are floats. Back in level editor scene, that error goes away. Okay, so we generate this game object, but then next thing we need to do is we need to attach this to the mouse cursor. How the heck do we do that? The way that I like doing that is by creating a component that is object list. This component doesn't live inside any object. It's just sort of to organize our code. And I'm going to call this component, so we'll go into here, call this mouse controls. This is never visible to the user of the engine. It's just for our own benefit when we're organizing our code. And inside this mouse controls, it basically holds all the information we need in order to manipulate objects and the screen. So this is basically where any sort of control you want to do with your mouse will be living inside of here. So what we're going to do is we're going to say holding object equals null. Holding object is like whatever object the mouse cursor is holding, okay? So I tried to name these pretty similar to what you would think. Now we're going to say pickup object. And we're going to say this takes in a game object, go. Then we'll say this dot holding object equals go. And we'll say window dot get scene dot add game object to scene. And we will say the game object that we just added. Because if you pick up an object, we want to make sure that we have now added it so that it is visible to the scene too. We'll see what I mean too, because remember we have to get this new game object visible to the render and everything, and this is how we're going to do it. Then we're going to have another function, void place, and this is just going to say this dot holding object equals null, which should place whatever object you're holding. In the future, I do want to change this though, and you'll see why in a minute too. Then lastly, we're going to have an update function. So we'll say public void update float delta time, and we will say if holding object does not equal null, this means we are currently holding some object. And then we want to say holding object dot transform dot position dot x equals mouse listener dot ortho x. See, it's a really good thing we did this. And then I'm also going to subtract 16. I think that's pretty good, just so that it's centered on the mouse. Then we're going to say holding object dot transform dot position dot y equals mouse listener dot get ortho y. And remember, this is like world coordinates, not screen coordinates, which is nice. And then we'll just say if mouse listener dot is or mouse button down, and we're going to say GLFW left mouse button. I think that's it. Alt enter to import that. That's wrong. It's GLFW mouse button left. There we go. And then hit alt enter to import that. So if they press the left mouse button, what we'll do is we'll say place. Simple as that, which will place the object because now it's holding it and it's not going to track the mouse, right? So what just happened here? First, we check and see if the mouse controls are currently holding anything, which means that it's not null. If it is, what we do is we snap the object's position to whatever the mouse object's current position is, and we do that for the Y as well. Then we just say if the user presses the left mouse button, place the object. What that does is it says this holding object is null, and then the next frame when we go into this loop, it's going to say, oh, the holding object is null, and then it's no longer going to be tracking the mouse, which means it's just going to stay where it was last at. And then this pickup object will literally just assign the holding object to that object, and then it will also add it to the scene for us. Now, there are a couple of complications we're going to run into now that we are doing game objects and components, which I will mention in just a moment, but let's just check and see if this works. So let's go into our level editor scene and actually hook up this mouse controls. So what I usually do is I go up here and I say mouse controls equals new mouse controls. We literally just create it up here, and that should be good. Then we update it manually down here after we'll do it before everything else. So we'll say mouse controls.update dt, and that should be good. We have it wired up and everything now. So if we click onto this, it's not actually going to do anything because we didn't actually hook up the last part, which is attach this to the mouse cursor. So then we'll say mouse controls.pickup object, and then we'll give it the object. And right now this object is not added to the scene, so when we tell the mouse controls to pick it up, it attaches it, and then it also adds the game object to the scene for us, which is everything we want to happen. So let's do this one more time. We pick up an object and we get it, except you'll notice the X and the Y, those are good, but I mean the X is good, but the Y coordinates are flipped. And why is that? Let's go into our mouse controls real quick. All right, so inside of our mouse listener, I did forget to mention. So when we are doing Ys, we do have to say window.getHeight minus getY, because Y coordinates are flipped from the way we're projecting it to the way that OpenGL, or the way that we get it in screen coordinates. So in screen coordinates, we get like 0, 0 up here, but in our projected coordinates, we're getting 0, 0 down here. So we do have to flip it in order to make sure it's right. But now that we have that flipped, it should look good. And this is way too big. And also, when I left click, nothing's happening. So we have to fix that too. Okay, and so the reason that the mouse isn't working right now, one of the things I did was I changed this to a 9. So we have 9 buttons, because I know somebody mentioned that we can hold up to 9. I think it might be more than that too, but that's not the reason it's not working though. So the reason it's not working is because if we go into our ImGui layer, so if we go inside of the ImGui layer and we take a look at our mouse listener, so we have set key callback, then we have set char callback, then we have set mouse button callback. Notice what happens. We're setting the mouse button callback to our window, and it's sort of taking the mouse button and not letting us do anything with it. And the reason for this is because GLFW, the way it works is you can only have one button callback. So what we're going to do is we're going to forward this message if ImGui didn't use it to our callback. So we'll say if not io.getWant mouse capture, or capture mouse, which basically means ImGui does not need the mouse event, like it didn't use it. Then we'll say call our mouse listener. So we'll say mouse listener dot mouse button callback, and then we'll pass it just all the same variables. We'll say window, we'll say button, which this is actually W, button, action, mods. So we're literally just forwarding all of these to our function. That way our function actually gets the event called, and that works properly. So now if we do this, and then if we click, it gets placed inside the scene wherever our mouse is, which is what you would expect. And then I have all these from when I was testing, and they just sort of got locked down there. But yeah, so we should actually do that too real quick, just so that we don't get confused again with the key controls and stuff too. So if we go back into that ImGui layer, and we'll notice that we also have a set char callback, that should be fine, but set key callback, this one we should also say if ImGui or if io dot get want capture keyboard, or we can actually just say if not. So if it does not want our keyboard input, then we'll do the same thing. We'll just forward this to our key listener. We'll say key listener dot key callback and pass it W key scan code action and mods. That way we get our key inputs too, and that should be good. I don't think we need anything else. We might want to do the scroll callback eventually, because I do want to do some zooming stuff that we could get done, but for now that's good. Okay, so we're in a good place. We can now click and drag objects in. Next step would be to, when I click on this, it actually pulls it up in our inspector over here. But before we do that, I do want to do another thing that is important, which is set up a global ID system. So let me pull this back up actually. Imagine that you have some object here, this brick object, and this brick object, it has some component breakable that holds a reference to the player object, like the actual player. What we want to be able to do is make sure that that reference to the player remains the same every single time the game is exited and loaded. And so in order for that to happen, we need to store a reference to that player. We can't store the player itself. Yeah, and I actually think this is probably going to be best with a drawing explanation. So I'm going to draw this out real quick, and then we will continue coding. Okay, so let's imagine that you have your player, and he's just hanging out right here. And like I said before, you have this brick. This brick has some component which retains a reference to the player, or what we want to be a reference, right? So this component, and then he has something called player, and this literally just points directly to that player. Now, the tricky part is, how do we get it so that when you exit, you save everything, right? So all this gets saved, serialized. And then when you load it, you want to make sure that you have the same reference to the player. You don't want to store like the address. So one possibility is this could be like some address in hexadecimal of whatever this player's location was in Java's virtual machine memory. That's not good, because we have no guarantee that we're going to be creating these in the exact same addresses at all. They're most likely going to be in different addresses. So we can't do that. And so what our serializer is actually going to try to do is it's going to do, okay, so we're serializing this component, then we get to the player, and it's going to try to just start serializing this player as a normal game object. So it's going to do all of its components, its transform, its everything, put it right in here. But that's a problem, because up here somewhere, we've already serialized player. Like, all that stuff is already saved. So then what's going to happen is this is going to be one game object, and this is going to be a ghost game object, okay? So it has a whole copy of some object that doesn't actually exist in our game world stored there. That's not good, because now all of a sudden this reference is nullified. It's no longer valid, right? So instead of doing that, what we want to do is we want to be able to say, hey, let's get the actual reference to this player. So we store something like a number, and this number is some unique identifier. Every game object has a unique identifier between 0 and whatever 65 million, whatever integer.max is. Every component has a unique identifier between 0 and 65 million, whatever. So that if you're storing references to different components, you get the same thing. Now, these can be the same. So we could have a component of ID 0 and a game object of ID 0. That's fine. But we can never have two components with ID 0. They all have to have a unique ID. Then when we're loading our game world, we basically just say, okay, this has a player ID, and we'll say player ID equals 2. Then we would also say, when we are serializing inside of our start method, we would say, okay, well, player equals scene dot find player ID. And what this would do is this would go into our scene, and it would go through all our game objects and find the game object with that ID. Then this is actually a true reference to our player and not this phantom object, and everything is right with the world again. So this is basically the whole reason that we need the global ID system. With that in mind, let's actually code it and get it to work properly. I'm going to apologize in advance if anything looks different. I'm sorry. My microphone actually was not recording, so I'm re-recording this bit because Windows just decides to disconnect devices and everything at random. Okay, anyways, so how do we actually implement this? Let's do component first because it may seem a little bit more straightforward. Inside a component, what we're going to do is we're going to create a private static integer. This is going to be called our ID counter. We're going to initialize him to 0, and then we're also going to have a private int UID equals -1. Now, ID counter, this is not associated with any specific object. It's not associated with a single component. This is associated with component class in general. UID, however, this is associated with every single component itself. This is associated with objects. So just remember the static modifier, make sure that this is global. This is unique to each object. This is good because now we can actually use this to start assigning different IDs every time we get a new game object. So what we're going to do is we're going to go down here and we're going to say public void generate ID. And what this is going to do is it's going to say if this .uid equals -1, then what we want to do is this .uid equals ID counter ++. So what will happen here is basically we'll assign for the very first component, ID counter will be 0 and UID will be -1. So now UID is going to be 0 and then ID counter is going to go up to 1. For the second component, now ID counter is 1. So second component is going to be 1, ID counter will go up to 2, so on and so forth. This way each component gets a unique ID when we call this generate ID function. Let's create a couple more helper functions. We'll say int UID. Let's actually call this get UID. Just so that it's super clear. Return this .uid. And then we will also get a function public static void init int max ID. So this will be when we're loading levels and we want to make sure that ID counter is not 0 because we might have loaded some components that have that ID. And so basically what we'll do is we'll just say this dot, or we'll say ID counter equals max ID, which will assign it so that it is now going to be higher than any component. That way no components get duplicate IDs after we load a level. Okay, let's go into game object and actually hook this up. So every time we add a component to a game object, we are going to generate an ID for that component. So right here, say c.generate ID. If this component already has an ID, it won't generate a new one because it won't be -1. So that's sort of our flag to let us know, hey, this was loaded. We don't need to generate a new one. Inside game object, we're going to do something very similar. Go up here, private static int ID counter equals 0, private int UID equals -1. Exactly the same. Then down here, we're just going to say this dot UID equals ID counter ++. This could pose problems in the future because UID is going to be -1, and then when we're deserializing this, this gets called first, which means we assign this, and then we actually could be changing this after this gets assigned to whatever we saved. So we'll have to keep an eye on this. For now, it's okay, but this could potentially cause problems in the future. So yeah, and then we're going to do the same thing for our game object. We're just going to say public void, public static void init, and we're just going to say int max ID, and this will basically just say this dot, or ID counter equals max ID once again, and then we'll have a public int get UID return this dot UID. All right, so literally the same thing we just did there. Then what we're going to do is we are going to go into where we're loading our levels and make sure we hook this up appropriately. So when we are loading a level, what we will have to do is we'll go into here and we'll say int max go ID equals -1, int max comp ID equals -1. So we're going to try and find what the maximum ID we are loading in is, and then we will initialize at the bottom. We'll say GameObject.init with the maximum GameObject's ID, and we'll say component.init with the maximum component ID. So just make sure that we initialize them before we start adding new objects. That way these are the appropriate. And we have to say max go ID ++ and max comp ID ++, because we actually want to make sure that these are one higher than the maximum ID. That way we don't get duplicates. When we are looping through our objects, loading them in, what we'll say is for component C in obj's I.get all components. Let's go ahead and create that function very quickly. So if we go into GameObject, we'll just go down here, public list of component, get all components, return this .components. That way we actually can get the whole list of components when we are loading them in. Now this is all good, and we'll just say if c.uid is greater than max comp ID, the max comp ID equals c.getUID. So this will end up finding the maximum component ID, and we'll do the same thing for the game object down here. We'll say if obj's I.uid is greater than max go ID, then max go ID equals obj's I.getUID. And then this should initialize it and everything. And you'll see that this, since we're finding just the maximum, this isn't actually going to get us the one higher. That's why we need to do the ++ down here, just to make sure it's all good before we initialize it. Let's actually run this just so you can see what the heck is happening here. So I'm going to run this, save, and then if we open up our level.txt, you'll notice object 1 gets UID 0, and you'll notice that components, we get UID 0 for the first component, 1 for the second component of that game object. Then for object 2, we get UID 1, and then we get UID 2 here, and that's for the second game object. Now, let's go ahead and make sure real quick that we're getting the correct maximum IDs. So game object should be 2, and max comp should be 3. So we'll say max go ID, and then system.out.println max comp ID, because those should be higher, one higher than the maximum that we have. So if we run this, we'll notice we get 2 and we get 3. That's perfect. One more test. Let's go into level editor scene. And I am going to add one more component to our game object 1. So we'll say this.activeGameObject.add component new rigid body. This is just to test and see like if it's going to assign it a new UID that actually works. So if we do this and then we hit save, we'll look at our level.txt. Now object 1 should have 3 components. So we get UID 0, we get UID 1 here, we get UID 3, which is perfect because we have a UID of 2. So you'll notice that we're getting unique IDs for each one of these game objects and for each one of the components, which is what we wanted. I'm going to remove this now. But yeah, so this is our global ID system. This is the end of this tutorial. In the next tutorial, what we're going to be doing is probably implementing a snap to grid function so that our blocks are snapped to a grid, and we're actually going to start drawing a grid. So I have no idea what I'm going to do for that, but I'll think about it and find something that should be suitable for us. In the last episode, what we did was we implemented the drag and drop functionality of our level editor. This is great, but now we want a way so that we can actually order these on a nice tile map. So what we're going to do in this tutorial is start adding debug drawing facilities. So these debug drawing facilities, as you can see right now, are going to help you to draw lines just anywhere at any time. This is really helpful for things like physics when you're trying to debug like if a velocity is pointing the right direction or something, or even if you're just trying to debug different things about your game. So this will be a nice function to have in general, but it will also allow us to draw our grid lines. So hopefully what we'll get to is having a grid drawn by the end of this. If not that, we will have a nice debug drawing facility at the very least. Okay, so let's get started. We're going to look at how this works and then we're going to actually implement it. Now, I know what you're probably thinking. You're probably thinking, drawing lines, what kind of explanation do we need for that? And normally I'd be like, yeah, you're right. I mean, drawing lines is one of the simplest things ever. But in OpenGL, nothing is simple. And if you go into lower level rendering APIs, it gets even more complicated. So, how do you draw a line? Well, let's start with the basics. So, say we've got some lines here. We know this is at x1, y1, z1. We know that this is at x2, y2, z2. And remember, we do need these z coordinates because OpenGL is a 3D rendering API. So no matter what you want to do, we're always going to have those. This line has the same thing, just some different coordinates, and this line also has some different coordinates. Now, how do we send these to OpenGL and then tell OpenGL, hey, I want you to draw some lines here, here, and here? Well, there's a couple ways we could go about it, okay? So the way that I first did it was I actually turned these into quads. So instead of drawing lines, what I did was I drew very thin quads, and I did the same thing over here, and then I would do the same thing over here. And the benefit to doing something like this is you get control over each individual stroke width. You can make these as fat or as thin as possible, and you get more control over the way they look. You can add joints like caps at the end of them if you want. You can add all sorts of other things too. You can get crazy with it because it's a piece of geometry now. It's not actually a line. And that's useful because if you want to have control and make your lines look nice, then you would probably want to do something like that. It's also a little bit more complicated. So what we're going to be doing is we're going to be using GL's built-in GL lines. Now this works similar to GL triangles. So if you'll remember, we had that function GL draw arrays, and we would pass it in GL triangles or draw elements in our case. This time what we're going to be doing is we're going to be drawing lines. And so what this expects is it's going to expect some coordinates. And so basically it'll be like, okay, vertex 1, vertex 2, which would respond to this vertex 1, and we'll say this is vertex 2. This is V3, V4, V5, V6. So then it would expect V4, V3 or V3, V4, it doesn't really matter, and then V5 and V6. And this would all be passed in one big array. Now remember, in GL we define what our vertices look like. So in our case, what I'm going to do is I'm going to say one vertex actually looks like this. It's going to contain X, Y, Z, R, G, B. So we will have our position and we'll have the color of the line for that vertex. And the color will stay the same for two vertices. So this will be red, this will be red. That will never change, but we can't really tell it that. So what we'll actually be passing in is 6 floats for each of these vertices. And this will actually be an array full of 1, 2, 3, 4, 5, 6 times 6, 36 floats. So this would actually be like 36 numbers, and it would just look like X, Y, Z, R, G, B, X, Y, Z, R, G, B, over and over and again until we got all 6 of these vertices done. The reason for that is because we're going to be sending these as something called the VBO, the VAO, right? So we're going to be creating this VAO, which is just an array object inside our GPU. Then we're going to bind a dynamic VBO so that we can upload these dynamically every frame, just like our batched rendering. Now, one more thing that I'm going to mention before we start coding is there is one other thing that you typically want to control. I didn't think about this at first. I was reading through Game Engine Architecture 3rd edition, I think, and the author was one of the guys who worked on Naughty Dog's Uncharted series. And he gave a description of their rendering API, and I saw something that I really liked. And it was like, okay, if you want to draw a line, what you need to pass in is the start position, the from to, so you're drawing it from here to here. You want a color, and you want a lifetime. I never thought about this part, but it's super useful because there are many times when you want to shoot a line out and you want to be able to see that for maybe like 10 seconds just that you can see where this is, but you don't know, but you can only draw it once, right? So like if your physics code hits at the ground and you want to draw the ray that it's supposed to bounce off at, you're probably going to get one frame to draw that ray. So you would draw it and say, hey, stay on the screen for 10 seconds, and then it'll stay on the screen for 10 seconds. So lifetime is super useful. One other thing they had is stroke. I did add that, but since we are doing it With GL lines, at least for now, we can't actually individually control the stroke for each line. If we were doing GL triangles and we actually made these into quads, we could, but we can't do that. So we will stick with just these 4 parameters for now. Okay, so that's sort of the basics. Let's actually see how to draw this or code this. Okay, so first thing I'm going to do, let's go into our render package, create a new class, and we're going to call this line2D. So line 2D is going to be just our 2D lines. We're going to need a few variables with this. Let's actually do vector 2f from private, and you can also call these start and start and end if that makes more sense to you. It doesn't matter. And then we're going to have a private vector 3f color. I eventually do want to have an actual color variable that wraps a vector 3f, or maybe not even that, just a color variable. That's in the future though. And then an integer, and that is our lifetime. Then we will actually, let's just say code generate constructor. We'll give it all these variables because we do want that. And then we're going to say code generate, and we're going to say getters for these 3, and then that should be good. Okay, so now we have our class done, and I like my constructors to actually be up top. So I'm just going to move that. Okay, and then next thing we're going to do is create another new class, and we're going to say debug draw. But first, one more function. Okay, so we actually do need one more function. We're going to call this begin frame. And what this begin frame function is going to do is it's basically going to say the lifetime minus minus, and then we're going to say return this dot lifetime. So the lifetime of a line is determined in frames. So if you're running at 60 frames per second and you say 60 as the lifetime, you'll get your line for 1 second. If you're running at 30 frames per second and you say 30, you'll get a 1 second line. So basically we're just binding the lifetime directly to the frame rate because it's easiest that way. You could technically do it in real time, but I didn't really care because I know my frame rate and I think most of you know what your frame rates are. So we will run just like that. Next, let's create a new class. We're going to call this debug draw, also in the render because these are rendering facilities. I think it makes the most sense. Now this debug draw is going to need a lot of the same things that our batched render needed. First of all, we're going to declare a private static int max lines, and I'm going to say 500 for now. We may increase that in the future. It's the maximum number of lines that we'll be able to hold. After that, we'll just simply start redrawing, removing old ones and drawing new ones. It's no big deal. Then we'll say private static list line 2D, and this will be our lines, and this is going to be a new array list. And since we do know how many lines we need, you could make that an array. It's a debug facility, so I don't see any need to worry too much about performance here. It's nice to have good performance, but you don't have to worry too much. Then we are going to have 6 floats per vertex, just like I said in that thing, 3 for position, 3 for color, and we have 2 vertices per line. So how many floats do we actually need? For our float array to contain all the numbers, well, we need vertex array equals new float max lines times 6 times 2. So this will hold the right amount of floating point numbers for 500 lines if we just do that. Okay, and then we will need a shader. So we'll say private static shader equals our asset pool get shader, and we're going to create a new shader. It's going to be called asset/shaders/debug line 2d.glsl. We'll create that after we actually get everything else up and running, but that should be good for now. And then we're going to need just a couple more variables. We will need a VAO ID and a VBO ID. So we'll say VAO ID and private static int VBO ID, and we're going to have a Boolean variable that lets us know if we have already initialized all this on the GPU yet. So we're just going to call that started. And next, we're actually going to create that start function. So public static void start. Everything in here is going to be static too, because this is a purely static class. First of all, what we want to do is we want to generate the VAO, so the vertex array object on the GPU. So this is going to be like all the initialization stuff of just getting the information onto the GPU, or in our case, getting a buffer onto the GPU. So a buffer of this size so that we can always upload to our VBO and not have to worry about not having room for our data. So we'll say VAO ID equals glgen vertex arrays. And I'm going to hit Alt-4 to enter that. And I always do the one without the C. I actually don't know what the C stands for. So GL30. Sometimes I've messed up. It doesn't really matter. So don't worry if you get the wrong one too much. Then I'm going to say bind vertex array VAO ID. Next, we're going to create the VBO and buffer some memory. So we're going to ask for some memory inside of our VBO. Say GL gen buffers. Alt enter, just to import that. Then I'm going to say GL bind buffer, and this is an array buffer. And we are using our VBO ID. Alt-4, enter, and enter. Okay, and then we're going to say GL buffer data, and we're going to take in an array buffer once again, and we're going to buffer our vertex array.length. Then you'll notice it says usage, which is GL. Don't forget, we do need to multiply this by bytes, so we need to specify the length in bytes. And then we set our usage, which is GL dynamic draw. So that will just make sure that we can re-upload vertices because we are going to be building this every frame. Okay, and then we're going to enable the vertex attributes, vertex array attributes. So we'll say GL vertex attrib pointer. And this is going to be our 0th index. This is going to be size 3. We're just going to manually specify all this stuff. GL float, and this is not normalized. The stride will be 6 times float.bytes, I think. Yep, this has to be in bytes, so it's 6 times float.bytes since we have 6 floats per vertex. And then the pointer is just 0 because this is our first one. Then we'll say GL enable vertex attrib array 0. Once again, I'm just going to copy this actually, paste it, do the same thing, and then this is going to be index 1, and I think it's actually all the same except for our pointer. This is 3 times float.bytes. So remember, this is just declaring so that our shader knows where to look for each thing. This is our position, this is our color, they're each a size of 3 floats, X, Y, Z, this is RGB. We don't care about alpha in this case. And then we're just saying it's a float, and this is the total size. We have 3 plus 3, so we have 6 floats total for each vertex. Multiply it by bytes so that it knows what size it is in bytes. This is offset from 3 from the 0th position. This is offset 0 from the 0th position. So that's what all that means. And then we'll do one more thing in here too. I'm just going to put to do set line width. I'm going to wait for that just so that you guys can see exactly what it's doing. Now, we're going to have 2 main functions that sort of control how all this works. We're going to have a public static void begin frame and a public static void draw. So begin frame will just sort of check and see if we need to remove any lines and remove them if we do. Whereas draw will literally just draw the lines. It'll create a bunch of lines and upload it to the GPU inside of this VBO. So inside a begin frame, this one's not too hard to get. One thing we do have to do is we have to say if it's not started already, we want to make sure we start and set started equal to true. So I thought, oh, I didn't make this static. I was like, why can't I find that? Okay, so make sure this is static, your started variable too. Everything is static in here. Okay, so basically this just makes sure that we actually have space on the GPU to upload our lines, just in case we haven't done that already. So it'll allocate the space and then we can start drawing in here. And we're guaranteed that begin frame is going to happen before draw because we need to call this first. So next thing we're going to do is remove all the deadlines. So remove deadlines. We're literally just going to loop through int I equals 0 until I is less than lines.size, I++. Make sure you don't use a for line in lines like a for each loop in here because we will be removing as we're incrementing, which means that the order can be messed up. So you need to make sure this is correct. Then we'll basically say if lines.get I dot begin frame is less than 0, so their lifetime has expired. We'll say lines dot remove I and then I minus minus. So basically what's happening here is we're going forward through the loop. If we find a deadline, we remove it and then we go backwards one so that we're actually onto the next line, right? Because if you have an array that looks like this, you're going through, you're here, then you're here, then you're here. Oh, I have to delete this one. Then you need to move back one so that the next time you're on this guy. And that's basically what we're doing. Okay, so that's all we have to do when we begin a frame. When we end a frame or when we draw, that's actually the harder part because we do have to upload all the data and generate all the data every frame. But it's not too bad. It's actually pretty straightforward. So first we're going to check if lines.size is less than or equal to 0, we'll return. We don't care about drawing anything if we don't have anything to draw. Then we're going to say int index equals 0 for line 2D, line in lines. We're going to loop through all the lines. Each line has 2 vertices. So we're going to say for I until I is less than 2, we have 2 vertices. Vector 2f, the point that we're currently working on, or the position, call this position, equals, if I is 0, we're going to get line.get from. Otherwise, we'll get line.get to. So this is just that we get the right position, right? So we get from, first time we go through this loop, then we get to. Just save some time. You could write this all manually outside of a for loop, but this is a little bit easier. I'll say vector 3f color equals line.get color. So we get the position, we get the color. Those two things are good. Now we want to load the position into our float array, and we want to load the color into our float array. So I'll say vertex array index equals point.x, position.x, vertex array index plus 1 equals position.y, vertex array index plus 2 equals position. Actually, we're just going to set that to 0 because we have a vector 2f for our position. Let's do -10 actually too. I don't think this matters very much because we don't have depth enabled, but that might come in handy later. So then we'll say vertex array index plus 3 equals color.x. And I'm actually going to just duplicate that a couple times. Y and Z. And then this is going to be 4 and 5. And then after we finish all that, we'll say index plus equals 6. That way the next time we go through, the index will be appropriate. And then every single time we go through a line, the index will just update according to whatever vertex we're currently on. So we're just filling in all the vertices, and here it's exactly what we're doing. Next, since we just generated all that data, we want to bind our VBO and upload the data to the GPU again. So we'll say GL bind buffer, GL array buffer, and we're going to pass in the VBO ID. And we're going to say GL buffer sub data, and we're going to do GL array buffer. I don't know if we've used sub data yet, but it's basically just buffering a sub portion. So we're just going to give it a portion of our array that has the lines. And for that, we can use a function in arrays that Java gives us. So we'll say arrays.copy of range. This will copy a certain range of an array. And we're going to say we want to copy our vertex array from 0 to lines.size times 6 times 2. What this will do is it'll actually create a copy of a vertex array from 0 to the most lines that we have. So remember, we could have up to 500, but we'll only have lines.size at any given moment. And then we just upload that to our GPU. Next, we want to use our shader. Because remember, this is our draw, right? So we're first generating all the data, uploading the data. Now we're drawing the data. And we're going to upload a mat4f projection. So we need to upload the projection and the view matrix, just like always. We'll say window.getScene .get or .camera. Okay, there we go. .get projection matrix. And then we're going to say shader.upload mat4f view. And this is going to be window.getScene.camera.get view matrix. Okay, so we upload the projection and the view. We want to bind the VAO now. So we'll say GL bind vertex array VAO ID. And then we're going to enable the vertex attribute arrays. So let's enable 1, 0, and 1 because those hold the position and the color respectively. We're going to draw the batch. So this is a batch of lines that we're drawing. GL draw arrays. And we're going to say GL lines. So this is where we have our first big change. We're drawing lines now. We're not drawing triangles. We're going to say 0 to lines.size. And you don't have to worry about this being too slow too, because even though it's not using the rasterizer, I looked some stuff up, and they might be something called using something called Bresenham's line algorithm to draw these lines underneath the hood. I'm not sure if that's true or not, but this is basically an optimized line drawing algorithm, which is nice. Because you can't draw a line the same way that you would draw a triangle, which is called rasterization, right? if you have a triangle that looks something like that, you're going to fill it in line by line, whereas with a line, you just fill in like a pixel or two every time. So it's a little bit different. Okay, so after we do that, we're going to disable the location. GL disable vertex attrib array 0 and 1, and then we're going to say GL bind vertex array, disable that. So we bind 0 to get rid of that, and then shader.detach. Okay, so we'll just say unbind shader. So this should draw our stuff. This isn't anything new, but I know that if you haven't been working with this stuff, it can be a little bit confusing. But basically, we just upload the position, upload the color to our copy, which is inside vertex array. So this is our local copy, right? We have this copy here. Then after we fill in our copy, we say bind the VBO, then we upload it to the GPU using this GL buffer subdata. That way, when we call GL draw arrays, it actually draws it. And notice too, this is different than GL draw elements. If we go to our render batch, when we're drawing inside here, we're doing GL draw elements. And the reason we're doing GL draw elements here is because we have this indices buffer. And so this indices buffer is also called elements, and that's why we call it GL element array buffer, but it's really just indices. And this is the reason it saves duplicate vertex data, but since we're drawing lines, these each have 2 lines only, or 2 vertices only, so there's no way we could really save data unless we search to see if any of them share a vertex, which would probably waste more time than just uploading the extra vertex at that point. So that's why we do GL draw arrays instead of draw elements, because we're just passing in the raw data instead of an index buffer. Okay, so that's that. Now let's actually add in, I'm going to call this our add line 2D method. So we're actually going to come up with a whole suite eventually. So we're going to have like add box, add circle too. But for now, we're just going to say add line 2D. Just to get this out of the way. We'll say public static void add line 2D, vector 2f from vector 2f2, and this will be our default one. So we'll kind of come up with a few each time of overloaded ones, which will be nice when we ever want to use this. So we're going to say add line from 2, and then we're going to actually have a few more. Let's create the full one first. So add line 2D, vector 2f from, vector 2f2, and then we're also going to be using a color and a lifetime. So we'll say vector 3f color and int lifetime. So this will be our full sort of method. Okay, and then I'm going to say this default color we'll use is just green, so 0, 1, 0, and default lifetime is 1 frame, so we'll just do that. I'm going to add a to-do here, add constants for common colors. So we should do that eventually so that we just have like, we can say constants.green instead of doing this, which would be nice. Okay, but this is fine for now. Copy that. We're going to do one more overload where they can just pass in a color. And then I'm going to say color here and take that out. So basically these are just 3 versions of the same thing, but you can add in just your from to 2, and then you get default green with 1 frame. This one you get your color, but then just a default time of 1, and then this one you can specify everything. And then we're going to say is if lines.size is greater than or equal to max lines. We have no more room. We'll just return. We won't actually add the line, but if we can, we'll say debug draw dot lines dot add new line 2D from to color lifetime. Nice and simple. We're literally just adding this. This is our list of lines. So we basically check and see if we have enough room still. And if we do, we just add it to our list, a new line 2D, and then it gets dynamically created inside of our draw function and drawn to the screen. Okay, so where do we actually call that begin frame in that draw function? Well, I'm just going to do it in the window because this is the easiest place to do it for now. But basically, we can go down to our loop function, and every time right before we clear the color, what we'll do is we'll say line or debug draw.begin frame. And right before we update, so actually this is an update and draw. So before we draw everything else, we'll draw our debug lines. We'll say draw.draw. So this will draw our lines, and then we'll draw everything else after that. That way, these are always behind everything. You could make it so that they're always in front of everything too, and we'll talk about how to do that in the future if you want to. But yeah, so that should draw it, but we're not going to get anything drawn because we don't even have a shader done yet. So let's create a shader real quick just so that we can actually draw this. I'm going to go into here, create a new file, and I think I called this debug line 2d.glsl. Believe. I could be wrong. Okay, so first we say hash type vertex and hash type fragment. Remember, this is sort of our own special syntax that we added. Then we're going to say version 330 core layout and location equals 0 is our vec2, and this is our position. So we get position and layout 0, and this is actually a vec3, not a vec2. We'll say location equals 1 is in vec3 a color, and then we're going to say out vec3 f color. We're going to pass that to the fragment just so that it knows. Then we're going to take in our uniforms here. So we'll say uView uniform mat4 u projection, and then we'll have our void main function here. Okay, so then inside of here we'll literally just say f color equals a color, pass the color through, and then GL position, so this is setting the position that will be our sort of final position, is the projection times the view times our a pose. So we just need to make sure that's a vec4 though, so we add a 1 just to normalize that. Remember, projection, view, position, or model, I guess you could call this. But yeah, and that will give us the correct position, correct color. Now we need our fragment shader so that it actually draws these onto the screen. Once again, version is 330 core, and then we'll say in vec3, we're getting an F color. Out is our vec4, this is our final color, and then we'll say void main, and very simple, we'll just say color equals vec4, F color, and 1. So always have an alpha of 1, and we literally just pass the color through. Nothing fancy, we're not going to do anything fancy, it's just lines, you know? Okay, so that should be a good fragment and vertex shader for us, though. We should actually have functionality in here now. So let's test this out. Let's go into our level editor scene. And I am going to go up here to our init method and say debug draw.add line 2d, new vector 2f, 0, 0. This should be 2f. 2 new vector 2f 800 800 just so that we're sure to see it. Give it a color of red and a lifetime of 120, so it should be 2 seconds on my screen. I'm running at 60 FPS. If I run this, we should see a line, but we see nothing. So let's figure out what's going on there. So it would help if we're actually drawing the line. I just realized this is down here where we actually break out of if our level is loaded, which it's currently being loaded every frame or every time we run this. So let's copy this and we will paste it right here. And one other thing I changed too, you may or may not see that too. It's very faint and it just disappeared because it just died. One other thing I want to mention is I did change our vertex position. No, I didn't. Okay, so this is still -10. Never mind. Okay, but you may have noticed that the line is very thin, so let's get rid of this to do, and I'm going to say GL line width, and if you bump this up, you'll notice that the line will get fatter. So if we do that at like 4.0, it's a pretty fat line, and it just disappeared. I think I'm using like 2.0. I think I like that the most. Yeah. So that looks the best to me. It's nice and simple. And let's just check out how nice it is to have this facility too real quick. So I'm going to get rid of this real quickly. Let's go down here and let's set float t equals 0, 0 f. And then inside here, I'm going to say x float x equals, I'm going to say float math.sign of t. So what we're going to be doing here is we're going to be drawing a circle with a radius of 200. I'm going to say plus 600 and then float y equals float math.cosine of t times 200, 0.0f plus 400. And then we're going to say t plus equals 0.05f, not 5t. And then we're going to say debug draw to add line to d. And we're going to say new vector 2f, 600, 400, new vector 2f xy, and new vector 2f We're going to make it red again. Let's make it blue. So 0, 1, 0, 1. Okay. And then this is going to have the default lifetime of 1 frame. So it should be drawing 1 line per frame. And you'll notice we get this cool spinning line. And another cool thing that you can do too is if we go up here and change the lifetime to, let's say, like 10 frames, we'll get a cool little blur effect. There we go. So this is pretty cool. Like, the reason we're getting this effect too is because the lines are actually lasting for 10 frames each now, so they're not dying. So those are actually 4 different lines, right? And this will allow us to do so much in the future when we need to do some sort of debug drawing and everything. Very useful to have, to be able to just anywhere in your code say, hey, add a line, and then it adds the line in world space too, by the way, that you need to see. So we'll use this in the next tutorial to actually draw our grid, but for now, this is it. In the next tutorial, we're going to be doing our snap to grid function so that we can actually snap sprites to the grid, and that should be good. And then soon we will be starting our physics engine. So those are some things that we have to look forward to. In the last episode, what we did was we did our debug drawing facility, so we can now draw lines and stuff. In this episode, what we're going to be doing is drawing our grid and snapping items to this grid. So this is going to be the first step that actually makes our level editor feel like a level editor, where you can drag and drop things and you can have them snapping to the 2D grid of your choice. I'm going to go over some of the mathematics that helps us make this work and then describe exactly what's happening, and then we're going to go ahead and implement it. So let's get started. So drawing this grid is actually pretty simple. It's a mathematical formula that we can use to actually calculate any grid. Assume that this top left corner is 0, 0, and assume each grid has a width of x and a height of y. I'm doing this with variables because it will be important later on if we ever want to change the grid size. Now, the first thing we want to be able to do is, if we have a point in the world, we want to be able to snap this to one of these corners. Reason being, when we're dragging around an object, we want to be able to have the mouse be here, but we snap it to one of these corners so that we know that the object is within this square. Well, how do we do that? Say this point is at some coordinate 133 by 67, okay? Now we can already tell, and let's assume that these are concrete width and height. We'll say the grids are 32 by 32. Just for this example. Now we can already tell that neither of these is a multiple of 32, because 32 is a power of 2 and neither of these are a power of 2. So how do we get it so that this actually snaps to either this corner, it doesn't really matter, we just need it to snap to a corner, and then we can sort of jumble it around. Well, it's actually not that bad. In programming and mathematics, you have something called integer division. Integer division is basically saying something like, if I have 6 divided by 4, we're going to truncate that. Since 4 does not go into evenly to 6 more than one time, we're going to say that's 1. Now, we know in fact that this is actually 1.5, but we're just truncating and removing that part and just seeing how many times it goes evenly into that. We can use this to our advantage. Let's see, how many times does 32 go into 133? Well, we can say 133 divided by 32 equals 4, I think. My math might be wrong on that. And then we'll say, okay, how many times does 32 go into 67? Well, 67 divided by 32, that's 2. We get 2 pieces. Now, we can just multiply this result. So we know that we get 4, 2. But that's not the place that we want to place this, because that would be somewhere like right up here. So we have to get this back into 32 by 32 space. So to do that, we just multiply both of those by 32, and that gives us 128 by 64. And then that would actually be on one of these corners. So as you can see, getting it to snap to a grid is actually not that difficult. You literally just divide by your grid width, your grid height, then you multiply by that grid width and grid height. And make sure you're doing all this as integers, because if you do it as integers, then you will lose the floating point part, and that will give you one of these corners. So now that we know how to snap a mouse position on the screen to the grid, the last thing we have to do is figure out how to draw the grid. So the first thing we have to do is take into account the camera's position. So the camera will be positioned at some XY coordinate, right? And then we want to start drawing first this line, then we draw this line, then we draw this line, and we also want to draw this line, this line, this line. And so in order to do that, we need to figure out, okay, where's the first grid point from this xy? And to do that, we can actually do the same exact thing. We just say xy divided by 32 times 32, or whatever your width and height is. You would divide the x by the width and the y by the height. And then this will give you some xy that is actually right here. And then you can say, okay, this is my first x, this is my first y. And then what you do is you say, okay, draw from my first x, which would be right here, and then my first y, draw a line from there to my first x to my first y plus whatever the screen height is. So we'll say h. What that will do is draw a point from here. This is first x, first y, right? Then we're still at x, and then y plus h would bring us up to here. And then we can say, okay, also draw a line from my first x, my first y to my first x plus the screen width, my first y. What that will do is it'll draw a line from here all the way to here. So then we'll get that line. Then how do we get the next line? Well, we say the next line is actually the first x plus the grid width, GW, times whatever line index we're currently on. The next y is y plus the grid height times whatever index we're on. And so what this means is, okay, so if we're doing this, this is the first line, we would get first x plus 32, which would bring us to here. And we would get first y plus 32, which would bring us to this point. And then we would do the same thing. We would say, okay, go from this y all the way to here, go from this x all the way up to here. And then we continue doing that. So that gets us each individual point. The last thing we have to figure out is how many of these lines do we need? And once again, this can be solved with integer division. So how many of the y lines do we need is what I'm going to call these the vertical lines. Well, we need as many vertical lines as can fit within this width. If we have width and we have grid width, we can say width over grid width equals the number of vertical lines. That will give us, so we can fit however many grid spaces fit into here, we can fit however many of those just by dividing width by grid width. And then same thing for the horizontal lines. We just do our height over our grid height, and that will give us the number of horizontal lines that we can fit into this grid. So that about covers it, because now we know exactly how many lines we need to draw. We know how to increment through as we're looping through each line we're drawing. And we know how to snap a position inside the grid to one of the specific corners. Now that we know how to do all that, let's actually implement it all and code it. Right before we begin to code, let's actually fix this real quick. I have a to-do in here, a couple to-dos. First of all, I'm going to change this to ×2 so that we get smaller sprites because those were huge. And then I'm also going to change the texture coordinates because actually the texture coordinates for the X were flipped when I was dragging and dropping items onto the screen. So if we just switch the X's from 2 here and 0 here, that should fix the flipping of your textures, right? And then we can take those to-dos out. Next thing I'm going to do is I'm going to create a constants class inside of util. And really this is more like just sort of a, let's call this settings. Okay, I'm going to call it settings because it's not really constant. It's just going to be variables that are easy for us to modify. So we're going to call this first one grid X equals, or actually grid width equals 32. And in my experience, if you're working with a grid, you usually want it to have the same width and height, but we're going to do this just because. Why not? So they can change the grid width and the grid height dynamically, and that won't matter. Let's go and create one more class now. We'll go up to components. We're going to create a new class, and we're going to call this grid lines. This component will be in charge of drawing grid lines. Very simple. That's all it does. Now I'm going to say that this guy extends component, and we are going to say we only need one method, which is the update method. So we're going to override our update method, and this is where we're going to do all of the work. So we're going to need a couple of things. We're going to need our camera position, and we're also going to need our projection size. Now, what is the projection size? If you remember inside of our camera class, we have the projection matrix, and the projection matrix just tells our screen how big we would like it to be in pixels or in world units. So we have this concept of window width, which is completely different than projection width. Projection width is how big we would like our world units to be displayed in any window, and then depending on the window size does not matter. We will always know we have this many world units inside that window to be able to draw on. So that's our projection size. So let's actually go up here real quick. And we're just going to say, actually make this private. Private vector 2f projection size. And I'm just going to say this is a new vector 2f. And we're going to give it these properties right here, actually. So I'll just copy that, paste it right there. And copy this one and paste it as our y. Then I'm going to change this to use that. So we'll say this is actually projection size, not projection matrix, dot x. And this one is projection size, dot y. Okay. Then we're going to create a little getter just so that we can get that. We'll say public vector to f get projection size, return this dot projection size. All right, let's go back to grid lines. So now we can get the camera position, we can get the projection size, because those are the two things we will need to be able to calculate where exactly we should draw our first grid line. So we'll say the camera position is equal to the window dot get scene dot camera dot position. And then we'll say our projection size is equal to the window dot get scene dot camera dot get projection size. Now we can calculate where our first x and our first y are. We'll do this exactly how we said. We just divide by the grid width and we multiply by the grid width, the camera's position. So we'll say integer cast camera pose dot x over constants dot grid, not constants, sorry, settings dot grid width times settings dot grid height. Okay, and then first y is literally the same thing just for y. So we'll say first y is camera pose dot y over settings dot grid height times settings dot grid height. There we go. So this is exactly what we talked about. It's literally just going to snap it to one of those corners, which is perfect for our purposes. Now we want to figure out how many vertical lines we can have and how many horizontal lines we can have. I'm just going to truncate these to VT and HC. So vertical, horizontal. And this can be a little bit confusing. Just remember, vertical is up and down, horizontal is left and right. So how many up and down lines can we get? We need to focus on the X for that. And then for horizontal, we need to focus on the Y, which is why it's a little bit confusing. So the way we do this is we just say we'll use the projection size.y. So what's the height we have over the settings.grid height. And that's how many horizontal lines we can fit. See, I'm already messing up. So this should be X. This should be width. That's how many of the vertical lines we can fit. We focus on X. And then for horizontal, we'll say this is projection size dot Y over settings dot grid height. Okay, there we go. So now we have the first X, we have the first Y, we have the number of vertical lines we can fit, and the number of horizontal lines that we can fit. Now I'm actually going to say height equals projection size dot Y and width equals projection size dot X, and we'll just cast those to integers. And you'll see why in a minute. I'm just going to do it like this for now. Ease of use. Then we're going to say for int I equals 0 until I is less than, well, okay. So typically we're going to have more vertical lines than we are horizontal lines, but I guess there's a possibility that could not be true. So we'll say int max lines equals number of vertical lines is greater than number of horizontal lines. If it is, it's vertical lines, otherwise it's horizontal lines. So basically we're just seeing which one's bigger. I guess we could just do a math.max, yeah. Okay, so we're just seeing which one of these is bigger, getting the bigger one for max lines. Then we'll say for int I equals 0 until I is less than max lines, I plus plus. And then what we can do is we can calculate where our X and Y are going to be, just like we talked about in the video. So we'll say first, so we'll say X equals first X plus the settings dot grid width times our current index. This is exactly the formula we talked about. And then we'll say int Y equals first Y plus our settings dot our grid height times I. So 0th, it'll be at the bottom left corner. First index, this will be 1 to the right. This will be 1 up, so on and so forth. Then we'll actually draw our lines. So we'll say if I is less than number of vertical lines, we will draw a vertical line. We'll say debug draw to add line 2D. So we want to make sure that we're drawing from the x's. So the x needs to stay the same since this is a vertical line, and the y needs to go up. So we'll say we'll draw it from new vector 2f x y to new vector 2f x y plus height. And then that should be good. And let's give it a color too. So I'm just going to go up here, say vector 3f color equals new vector 3f, and I'm going to say like 0.2f just to give it a little bit of a gray color. And then right here we'll just say color. Then we'll say if I is less than number of horizontal lines, we will draw a horizontal line. Say debug draw to add line 2D. Since we're drawing a horizontal line, this time it's the x that's changing, the y needs to stay the same. So we'll say new vector 2f x y, new vector 2f x plus width y. And we'll give this the color too. Now, fingers crossed, this should actually draw the lines, but we don't have any way to do that yet because we're not actually updating this. So let's go into our level editor scene. And I'm going to go up to the top. And what I'm going to do is instead of having mouse controls be a mouse controls object, I'm just going to say this is game object. And we're going to call this level editor stuff. Okay, horrible name, but we may change that in the future. This is basically just going to have all of our level editor components that we need. And we need to give it a name. We'll just call this level editor, a empty transform, and a 0th z index. Okay, so that should be good. And then what we're going to do is inside of our init, we'll just say level editor stuff to add component, new mouse controls, and then level editor stuff to add component, new grid lines. This way we can just add components to this, and we know this will never be serialized because we're not actually adding it to our scene. And then we'll just say level editor stuff to update, and right here we'll just say level editor stuff dot get component, mouse controls dot class dot pickup object. And we may change that in the future, but it's good enough. Okay, so you can see it's kind of working. I clearly made a mistake when we're drawing the lines because we're not supposed to use x and y for our variables that are not changing. Let's go back to grid lines. I did x, y here. This should actually be first x and first y. And same thing down here. So first x and first y. And then this should be first y, and this should be first x. Okay, now if we run this again, that's definitely not the right thing either, but that's kind of cool. Okay, let's see if I can get this right this time. Okay, I finally got it. So this is x, this is first y, this is x, should be first y plus I. Okay, so you can see that the x does not change, and then the first y goes from the bottom to the top of the screen, and then in this one, the y does not change, and the x goes from the left side of the screen to the right side of the screen. So that is what we should actually be drawing. Now, if we run this, we get a grid. But you'll notice, if you can see my mouse in the left corner of the screen here, we're actually one off. And so the reason we're one off is just because when we're snapping, we're actually snapping to this corner. So to combat that, what we can do is say first x is actually this camera position over grid settings, all this stuff. And then what we're going to do is we're going to wrap this in parentheses. And then I'm going to take away this parenthesis over here. And then we're going to do the same thing right here. So what we're doing is we're actually moving these back one space so that we make sure to get all of them. Then we need to make sure that we're actually doing two more lines because we're going back one, so we need one extra line on the bottom and left and one extra line on the top and the right. And then right here we'll say plus settings.grid width times 2 and plus settings.grid width times 2. And this one should actually be grid height. Okay, so this way we make sure that we get the appropriate width and height as well. And then if we rerun this one more time, there we go. You notice that this is fully covered all around, which is good. And if we were to move our camera, we would also get the same thing. One more thing I'm going to do now. Actually, we need to go into level editor scene anyway, so let's go level editor scene. And I changed this to ×2. Actually, keep this ×4 because I do like it for the ImGui, but then when we're drawing it here, right here, let's not pass in sprite width, we'll pass in 32 by 32. That way we have the same width and height as our grid. That way when we drag something in, it actually fits inside of our grid size. Let's also stop drawing that line real quick because we know it works. No reason to keep drawing it. So I'm going to take this out and take all that out. Okay, now what we need to do is actually make it so that our objects snap to the grid, and this is actually really simple. If we go to our level editor controls or our mouse controls, right inside here, this is sort of where we're setting the X and the Y of our game object every single frame. So what we can do is we can just snap this to one of the corners, right? So what we'll say is holding object.transform.position.x equals holding object.transform.position.x over settings.grid width times settings.grid width. And let's actually wrap this in parentheses just so that we know we are doing this in a specific order for a reason. And what this should do is this should start snapping its X position. It won't snap its Y position yet, but if we go here, it's actually not doing anything. And that's because we need to cast this to an integer. So make sure to cast that to an integer. And I'm going to go ahead and just copy this, paste it, and then we'll do the same thing for the Y. We'll just say this is Y, this is Y, this is grid height, and this is grid height. There we go. And now if we run this and we click on an object, you can see as I move the mouse, it tracks to whichever grid position my mouse is in. This is really cool. This is like the beginning of some true level editor-y type stuff. We can actually sort of drag things in and start building a little level. And then we can drag some of these blocks up and everything, and it's all good. Now, there's a couple problems. First of all, one thing I'm going to do is side of our level editor scene, I'm going to get rid of those two giant squares because we know our alpha blending is working properly now. I'm just going to comment that out just in case we ever need to bring it back again. Then I'm going to delete that level file that we had. So I'm just going to delete level.txt. That way we get a fresh level. And the problem that I'm mentioning is basically if you drag in a bunch of stuff and just keep dragging stuff in, what you'll notice is if I exit and I re-enter, no, it actually worked this time. Let's keep dragging more stuff in. Well, I would if I could. Okay, that's a weird bug. So I was dragging stuff in, but it wasn't showing up. So that's another bug we have to fix. But also, if I just keep bringing stuff in, you'll notice that sometimes it doesn't save properly. And I haven't quite figured out what that bug is yet, but it's something I have to look into and that we have to fix because that's definitely not good. So let's see if it does it this time. Yeah, so see how this square is missing even though I filled it in? That's not good. What I'm guessing is there's something weird going on with when we're adding game objects and they don't get added completely to our list and it just doesn't serialize it for some reason. So we've got to fix that. But once we fix that, we have a level editor that we can drag and drop stuff into. Our next thing that we have to do is to have a button down here that says add component, where we can either add a component or we'll just update our prefabs object. I'm not sure which direction I'm going to go yet. But that way we can start doing our physics because then we can start bringing in objects with physics components and start building levels and testing to see if everything is working properly. In order to do that, though, we need a player controller to see if we can control a player. So we might actually go into animations, possibly, or physics. Let me know which one you guys would rather go into. So a finite state machine-based animation system or starting physics. And then we will start to do that next tutorial. In the last episode, what we did, I believe, was we were doing snap to grid. It's been a while. And this episode, what we're going to be doing is continuing our debug drawing facilities by adding debug drawing for boxes and circles, because it'll be helpful for the physics engine portion of the series, which I would highly recommend to also follow because we will be using some of the functions from that series, particularly in this episode when we're rotating boxes and stuff. Okay, but let's take a look at how we're going to do the drawing of the boxes and the circles, and then we'll go ahead and implement those. Okay guys, so I hope you can trust me when I say that drawing circles and squares should not be too difficult. It really isn't, especially with the help of our function jmath rotate. This function will really make our lives a lot easier. So for boxes, how do you draw a box? Well, first of all, what you need is a half size, right? Or a full size, right? Just the dimensions of the box. So how big is it in the width and the height? And then you need the center of the box. And so once you have both those things, you can actually draw a box just like this, right? And how do you do that? Well, you just go center plus half size, and then that gets you this point, center minus the half size, and then you just do this point plus the half size in the y, and then you do this point minus the half size in the y, or just anything along those lines. What that's going to do is it's going to give you these 4 points. So once you have these 4 points, you can also check and see if there's a rotation, right? So what if they want to rotate it 45 degrees? Well, if they want to rotate it 45 degrees, all you do is you rotate this point around this point. So rotate every single one of the points around the center by 45 degrees. Then you just draw a line from him to him, him to him, him to him, and him to him. And then you end up with a box. And of course, this would actually be rotated, because if we rotated all the points already, then it's going to be actually something like this, where you have some sort of rotated box and it works just fine. Okay, what about circles though? So circles, we're going to be doing sort of the same way. What we'll actually do with these is we won't really care about the center at first. So as you may know, there's something called the unit circle, right? And the unit circle is basically just like a bunch of points. You know, you have like this, something like that. And what does it make? Well, it makes a circle. How do you get these points though? Right? Because if we can get these points, then all we have to do is draw a line, draw a line, draw a line. And then once you draw a line between all of them, you end up with something that resembles a circle. And the more segments you have, the more circle-like it will be. Well, these points are actually really easy to get, right? This is just the 0.0 radius, right? So this first point right here is 0 radius, rotated 0 degrees. And then the next point would be 0 radius, once again, rotated by whatever increment you're choosing degrees. I'm going to say increment degrees. And the more increments you have, the smaller granularity like this is, the better a circle you will get. So if you're incrementing in, let's say, 30-degree increments, then you'll get 2 points between every single one of these, right? It'll be 0, then this would be 30 degrees, then you would get 60, then you get 90, so on and so forth. If you did it in 15 degrees, you would get an extra point in between there, and it would give you an even better circle. And so just changing this increment will really change how it works. Except the way that we'll think about it is we'll think about it in segments, right? So we'll think about it, we want 12 segments of a circle. And then to get our increment, all we do is 360, because there's 360 degrees in a circle divided by the number of segments. And then that will give us some number that we can increment by. And we'll literally just rotate 0 radius around the degrees. That'll give us a point. And then we'll draw a line between every single one of the points. And what we do to get it in the appropriate place is we just add the center. So like say the circle is actually located over here. Well, we just add the center to all the points, and then it will draw a new circle over here, just like it should. Okay, so that's a very brief primer. If anything didn't make sense whatsoever, just let me know, and then we can go over it in a little bit more depth in another tutorial, or I can help you out through the comments. Okay, let's try and code these now. I am back inside of our debug drawing facility, or debug draw class inside of our game engine. So I just added the stubs. You know, we have the add line 2D methods, and I added add box 2D and add circle methods, just so that we know what those are. What I'm going to do is I'm literally going to copy this, because we're going to have very similar parameters. And this is going to be like the final. Remember how we overloaded this a bunch of times so that you can supply different parameters? We're going to do the same thing with add box 2D. And we will take in, instead of a vector 2f from and to, we will take in vector 2f center and vector 2f dimensions. And those dimensions, like I said, is just going to be the size, like width and height. So x would be the width and y would be the height. And we'll take in color and lifetime once again. And now we'll actually be able to use this add line 2D method. And that's why these ones are actually a lot easier to add than it was to do the line 2D, because we can just reuse what we have already. So like I said, first we have to get all the vertices of the box. So, and speaking of that, that means we're forgetting one more thing, which is float rotation. So we also want to allow them to rotate the box by any amount that they want. And then I'll move these down so that you guys can see that. So they will be able to rotate this box as well. Let's go ahead and first of all, we'll say vector2f min equals new vector2f. We'll use the center dot sub new vector2f dimensions dot divide by 2.0f. And I don't believe we have divide. It's weird. It works in my original project. Maybe it's in a different library and I just don't know. We'll just multiply by 0.5f because that's the same thing. And remember, we wrap these in new vector 2f's. That way we're making copies and then we're operating on copies instead of the actual thing passed in. And so basically what we're doing here is we're just saying, okay, take the center and subtract half the size, which will get us the bottom left corner. Then we can do the same thing for the top right corner, except we'll just say add instead of divide. So we'll say to the center plus the half size, which is just dimensions dot multiply by 0.5. Half the size. Now using the min and the max, we can actually get every single corner of the box. So we will say vector 2f vertices, and we'll just initialize these straight out because we know we're only going to have 4 vertices. So we can say new vector 2f min.x min.y. Think about this. This is the bottom left corner. We'll get the top left corner next, min.x, new vector 2f, min.x, max.y. And then we'll get the top right corner, new vector 2f, max.x, max.y. Then we'll get the bottom right corner, new vector 2f, max.x, min.y. It's important you think about exactly how these are working, and I forgot an equal sign, because we will need to know what order we actually built these in, because we don't want to accidentally draw a line from the bottom left to the top right. That wouldn't look right. So now we can draw a line from here to here, here to here, here to here, and we get our box. Okay, now let's say if rotation does not equal 0.0. So if they have something that they want us to rotate it by, we'll say for vector 2f vert in our vertices, we'll say jmath.rotate that vert around our rotation about our center. And remember, this does operate on our vertices, so we don't actually have to do anything. So now all our vertices will have been rotated, and then we can simply just add the lines. We'll say add line 2D from vertices 0 to vertices 1 with our dimensions, or with our color and our lifetime. I'm referencing old code, which I have stroke width available to. And I'll copy these 3 times, and we'll say also draw one from 0 to 3, also draw one from 1 to 2, and you can also draw one from 2 to 3, which should be good. And of course, you could have just done, like I said, 0 to 1, 1 to 2, 2 to 3. If we look at this, 0 is bottom left, 1 is top left, and then bottom left 2, 3 is the bottom right, and then this would be top left to top right, and this would be top right to bottom right. Okay, so kind of a weird order, but it works. Let's test it real quick, make sure that we didn't do anything dumb and mess up. Well, that would be me, not on you guys, of course. So if we go into our scene, which I think is in Jade, no, it's in scenes. Okay, if we go into our level editor scene, I had this because I was testing some stuff. What we'll do is we'll just say debug draw inside of our update method, add box 2D, and we'll say new vector 2f 200 200 for the center, and we'll say new vector 2f. We'll make it like 64 width by 32 height, just so that's a weird height and stuff to make sure it's working, and we'll rotate it by 30 degrees. And then we'll say color new vector 3f 010, it's going to be green, and a lifetime of 1 frame, so that it just gets drawn every frame. Okay, and it's actually behind my stuff, so let me just move this to 400 200, and we should be able to see that. Okay, there we go. Yep, and we can see we got a box located at the correct position, rotated 30 degrees. Pretty cool. And we can do something cool. Just go up here and say float angle equals 0.0f. And then instead of 30, we'll put angle. And then right down here. And don't worry if you can't see this and stuff. It's just debug code. I'm going to delete all this in just a minute. And I'll say angle plus equals 10.0f times dt. So we'll have a spinning box now. We should. And if we look, you see that it is spinning very slowly. But nonetheless, let's up that just a little bit because we can. All right, and we've got a spinning box. Pretty cool. All with the use of debug drawing. Now let's go ahead and add our circle method so that we can draw circles as well. So if we go back into debug draw, actually before we do that too, let's add in the overloaded versions of these. So I'm going to copy these because it's basically the same idea, except this is going to be add box 2D now. So copy that, paste that, and then we want these things. These are the required parameters, and then everything else is optional. So then we'll do that and copy and paste them over this one as well. Then, and we still do have to add constants for common colors. Then what we'll do is we'll just copy this, paste, paste, and instead of from and to here, we will say center, dimensions, rotation. And then once again, down here, we'll say center, dimensions, rotation. All right, and there we go. Now we have the overloaded methods as well, so we don't have to call it with every single piece of information if you do not want to, right? You can just call it with the center, dimensions, rotation, and we'll color it green with a lifetime of 1 by default. Now the add circle methods. Once again, I'm gonna go ahead and copy this guy. Paste it right here. So for a circle, add circle, what we need is we need the center and we need the radius. And we don't care about rotations with circles because it'll look the same no matter what. Okay, so if we have the center and the radius, how do we get all the points? Like I said, we just use that unit circle. So we can say vector 2f points equals new vector 2f, and I'm going to initialize it to 12. 12 is our segment length. This is how many segments we'll have. And just to really exaggerate, I'm going to initialize it to 8 originally. So you can see how increasing the segments makes it look more like a circle. Now we'll say increment, just like I said, is 360 over points dot length. And we're using an integer. You could just easily use a float. It doesn't matter. But yeah, so just like I said, we do 360 divided by the length of our points, or how many segments we want, and that'll work. We'll say current angle equals 0. We're starting off at 0. We'll say for int I equals 0 until I is less than points.length I plus plus. Then we'll say vector 2f temporary equals a new vector 2f radius 0. That's the first point. Remember, we're just going radius 0, which is basically just the radius on the x-axis. And then we'll rotate this. We'll say jmath the rotate temp according to our angle around 0, since this is located at 0, 0. This is centered around 0, 0. And then we'll say points I equals new vector 2f temp dot add center. So then we add in the center, like I said, to get that. Now, how do we draw the lines between these segments? We can actually draw them as we're creating the points, right? But we just have to make sure I is greater than 0. So we'll say if I is greater than 0, then we will add a line 2D from points I minus 1 to points I. And we'll give it a new vector. Well, we'll give it the color and the lifetime that we have here. And so basically this will just draw a line from the previous point to the point we're currently on, which should be fine, right? And then lastly, we have to remember to say current angle plus equals increment. And everything should go smoothly. Then we'll have one more thing, which you'll see in just a second because we're actually missing something. Let's go into our level editor scene though and try this. We'll say float XY up here like I have. And then you can just say debug draw to add circle. Center, we'll say, is new vector 2f xy. Radius, we'll say, is 64. Color, new vector 3f 0, 1, 0, and 1. We'll say x plus equals 50 times 50f times dt, y plus equals 50f times dt. Okay, let's play this, see what happens. All right, so we get a very blocky circle, but look at this, we're missing one line segment. And also notice it's right next to our first point, right? If we remember, we said our first point would be the right angle, and we can actually see how this is true. If we make this 0 radius instead, you'll notice that we'll be missing a segment in the top right of the circle. So, and circle very loosely. See? So now it's shifted over to here. What's that telling us? It's telling us we're missing a line segment, the very last line segment. So what we can do is at the end, we'll say add line 2D. Points dot length -1 to points 0. So we add it from the last point to the first point to complete our circle. And then we'll just give it the color and the lifetime. And now if we run this, we get a full circle, which you can see. And that's not a circle, that is actually just an octagon. So let's make this a circle. Up it up to like 20 segments, and I think that should give us more of a circle looking segment. Yep, that is pretty circular to me. And you could of course go higher, but just remember the higher you go, the more intensive it is just to draw a single circle. So 20 looks good enough for me, but once again, you can change it if you want. Let's make those overloaded methods again real quick. I'm just going to copy these again from the add line 2D, and we'll paste them down here. And then we will copy these, paste them over this, paste them over this, copy add circle, paste, 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 and then we'll change this to center radius, and this to center radius. Now we have our overloaded methods too, and so we can do whatever we want. We can also change the color. If we want our circle to be red, let's just change it to red over here, and now we have a red circle. So yeah, that's great. This is going to be very helpful for our physics engine because we want to start checking to see whether two shapes are colliding, and now we can just draw shapes wherever we want. But it's also very helpful for other things in your engine, just visualizing where things are, maybe invisible things in your scene. So yeah, this has been drawing circles and boxes in 2D for our debug drawing facility. I hope you guys like this. If you did, please hit like and subscribe. And in the next episode, I'm not sure what we're going to be doing for the game engine, but for the physics engine, what we're going to be doing is we're going to be checking to see if boxes and circles are colliding. In the last episode, what we did was we covered how to debug draw shapes. And so now we can sort of debug draw all sorts of visuals that we may need, circles, boxes, lines, which is the majority of cases. In this episode, what we're going to do is we're going to start talking about frame buffers. And frame buffers are really important for things like deferred rendering. They are also important for things like docking. So this is specifically in preparation for integrating the docking branch of ImGui into our game engine so that we can actually implement docking and everything. But frame buffers are also nice to know about just in case you want to do some more advanced rendering techniques, like I said, such as deferred rendering or rendering in multiple stages. Okay guys, so let's check out what frame buffers are, and then we will go ahead and implement it in our code. Okay, so what are frame buffers? The concept is actually really simple. You can actually think of it almost exactly like a texture, right? So say you have your window. We'll call this the window. And say you want to render your scene, but like in our case, we want to render our scene to just a specific portion of the window, right? We want to render it right here. Well, how do we end up actually scaling our output, right? We want the output to be as if it was taking up the whole window size, and then we just sort of want to scale it down, just like if it was a texture. Well, the answer, of course, to this is to use a frame buffer. And so we can use a frame buffer by basically rendering to this thing. We'll call this our frame buffer. And so what happens is when we call all of our rendering calls on side of our GPU, what it does is it renders to this guy, which is actually just an off-screen buffer. And so it does all the techniques and everything. And then at the end, we say, okay, now draw a picture and draw it right here. And by the way, the texture ID is his texture ID. And then you literally just use his texture ID for this, and it draws your scene inside of this now scaled down image. The concept is fairly straightforward, right? We're just rendering to an off-screen thing, something that we never see, and then we're treating it as if it's a texture. We're treating this as if it is a texture. And then once we get that texture rendered, we just use that texture ID over here just like you would with a normal texture. Now, how do you create a frame buffer in OpenGL? Well, you create it just like any other buffer, right? We tell the GPU, hey, I want to buffer some memory. And you say, I want to buffer this much memory, and this is the type of memory that I am buffering here. And so you tell it the size of the frame buffer. So for instance, we could say just this size, right? Since we're only rendering to this small of a portion, we could say, hey, just create a texture of whatever this is. Let's say the whole window is 1920 by 1080, and this is like 600 by 480. Okay, and so we could say, hey, just allocate a texture of 600 by 480, but then you would have to reallocate a texture every single time that this thing got resized, and that's kind of not the most ideal solution. So what you could do instead is say, hey, allocate me a texture of size 1920 by 1080, and I will only be rendering to a sub portion of this, and I will only take that sub portion. Or you could do, like I'm going to suggest we do, just render to the whole 1920 by 1080 and then scale it down. Because if you're scaling to the maximum size that you will be in the ultimate case, then you'll get a better idea of what your frame rates will really be. Because sure, you'll be rendering like your editor and stuff, which could add some extra frame time. But if you're rendering to an actual smaller size texture, then it could be inaccurate of what the frame rates you would expect to see on a screen size this big are, because rendering to different screen sizes does actually take different amounts of time. Okay, but how does the GPU know how much size to allocate, right? We say we want 1920 by 1080. Okay, so let's just allocate 1920 by 1080 pixels. Okay, and then this is where our first question is, what the heck is a pixel? How much data does the GPU actually need to memory? Is a pixel just one integer? Is it 2? Is it 3? Is it a floating point number? And all these different numbers have different underlying data sizes, right? An integer is 32 bits typically, can be 64 bits, and so on and so forth. So what we have to do is say, hey, by the way, this buffer is specifically a 24-bit information for our color, and we'll save 8 bits for something called a stencil. And do you actually need this stencil right now? I would say no. You could just say, give me 32 bits of color, and then this would be one group. So you could say this or that. The GPU actually gives you some presets that you can use for the memory layout of these. And this stencil is used for different types of things. You can use it for shadows or outlining objects, like a stencil, masking. So it might be good just to use this preset just in case we ever do want to use something like that. But we tell the GPU, hey, 24 bits for color, 8 bits for stencil. Now it knows how much size to actually allocate for our GPU. There's one further thing that we can do to optimize this a little bit more. So in addition to the frame buffer, which is this is our frame buffer, we can also tell the GPU, hey, we're also going to use this render buffer object, an RBO. Remember, we have those VBOs, those VAOs. This is another one of those things. And so the render buffer object is useful for the GPU, because what this tells the GPU is, hey, by the way, this is some data that we're never going to read from. You only need to write to it. So the GPU can actually optimize this render buffer object a little bit more. And that makes rendering a little bit faster. Because if the GPU knows we're never going to be sampling from this render buffer object, we're just going to be asking for all the data at once at the end when we're texturing, then it knows it doesn't have to do weird things like store the color in PNG format or something. Not necessarily PNG format, but it stores it in a friendly format that it can get back to us. Instead, it can store it in a compressed format that is specific to your GPU, or it's OpenGL's underlying format for their pixels. And since they can do it in a compressed version and not having to worry about decompressing that, then they can actually write to it much faster and everything. So we will be creating this frame buffer, which is going to be very similar to how we did VAOs and VBOs. And then we will be attaching a render buffer object, which will help us when it comes to speed. This will speed it up just a little bit. Okay, so with that in mind, let's actually try and create a frame buffer and then render things to a frame buffer and see what happens. Very quickly, before we begin and before I forget, I do want to mention that there was an issue with this. Remember, sometimes when we would run this and you would save the file, you wouldn't actually save all of your scene. Like there would be random objects that were disappearing, quote unquote, but they weren't actually disappearing. What was happening was it just wasn't being displayed properly. So you would run it and then all of a sudden one of these objects wouldn't really show up. And so I fixed that, and the way I fixed it was by just changing a few different lines. So the problem is with the way that we're saving textures right now, which we have a to-do right now to save them differently. And this is exactly why, because you get bugs like this. But basically, the first change I made was inside of the renderbatch.java. I changed this line to if textures.i equals to this. So if we go into there real quick, render batch, and we go down to this line where we were checking, well, not that line, this line, where we were checking to see if we already have the texture. If you do equals on two objects, what you're doing is a comparison of addresses. So it would compare like the address of the actual object, which would be something else. But basically, if you have two different objects, it's going to return false. So this is better because now we can use our own method, which brings me to the next change I made, where I added this public string get file path to our texture. This is inside texture. And then I added this override boolean equals method. So if we go into there real quick, I'll let you take a look at that. So if I go to texture, I just added a get file path method. So just a getter for the file path. Then I added this override public boolean equals object O, and all this is Java's standard way of overriding the equals method for two objects, so we can basically define how the equals function works. So we just say if O, the other object, is null, return false. If the other object is not an instance of a texture, return false. Otherwise, we cast it to a texture, and then we check and see if they have the same width and height. We check and see if they have the same ID, and then we check and see if the file path is the same, and we just return whether all those are true. So it's just a bunch of ands, you'll notice, and I'll move that down as well so you can see it in full. But yeah, so add this function, add those couple changes I talked about, and you should be good. No more disappearing objects. Okay, now on to a frame buffer. So let's get started by creating an actual frame buffer class inside of our render. Go up here and say frame buffer. And this is going to be our frame buffer class. When we create a frame buffer, let's take in a couple things. So we'll say public frame buffer, and we will take in a width and a height. How big do you want this to be? And like I said, ideally you would want to make this your screen size. So whatever your maximum monitor size is, that is what we will have our frame buffers to be. And up here, I'm going to say int FBO ID equals 0 initially. And this is private. So this will be our ID for our FBO, our frame buffer object. Now let's just generate it. So like I said before, this is very similar to how we do the VBOs and the VAOs. It's literally the same exact concept. So we'll say FBO ID equals GLGen frame buffers, which will generate the frame buffer object for us. It doesn't have any space yet, and make sure frame buffers does not have a capital B. So this will just give us like an object ID that we can use, and then we'll say GL bind frame buffer, and we will say GL frame buffer and FBO ID. And we'll hit Alt 4 to import all this stuff. And once again, Alt 4. Next, we're going to create the texture that we're actually going to render the data to. So create the texture to render the data to and attach it to our frame buffer. So we do this just the same way that we would any other texture, but we're going to simplify things a little bit more. So what we're going to do is we're going to say up here, private texture, and that's null initially. Then we'll say this dot texture equals new texture, and I'm going to pass it the width and the height. And we're going to create a new constructor for our textures so that they can just take in a width and a height, and that is all they need to take in. So let's go to texture, and we will do something very similar to this init with the file path. Instead, we'll say public void or texture, and this is going to take a width and a height. Since we're doing this, we should probably create a default constructor, which just does nothing. So we'll do the default constructor and say text ID like equals -1, width equals -1, height equals -1. Just in case anyone uses a default constructor, they'll get an error because this won't work properly, and we don't want it to work properly. Okay, and then what I'm going to do is I'm actually going to copy our init method, but it's going to be a little bit different. So we'll copy all this, then we're going to get rid of all the STB stuff because we don't actually need that. We can get rid of almost all of this. I'm going to say get rid of it up to this GL text image 2D, and then we'll get rid of all of this as well. There we go. And then this should be all we need. We just need this text image 2D. We need the GL gen textures, and we're going to set file path to generated, just so that we know that this was a generated texture. And then we're basically going to go through the sort of same process, right? Except what we do here is we're going to say, instead of passing in the width and stuff that we got from STB, we're just going to pass in width, and we're going to pass in height. And then right here, where you would normally pass the data, we're going to pass in null or 0, which is another word for null in C++. So they accept 0 instead of null. But basically what this does is it says, hey, GPU, I want a 2D texture. I want it to be RGBA. But in our case, we actually just want it to be RGB because we no longer care about the alpha. I want it to have this width. I want it to have this height. And once again, RGB. And then it's going to be an unsigned byte. And we are not giving you any data because we don't actually have any data yet. So just allocate the space. And what this will do is the GPU will then say, okay, I'm going to create some big array, and then it'll have enough space to hold all this, and it'll be stored within this texture ID, which is exactly what we want. So this works. The reason we don't do the text parameter I, so all this stuff, is because if you're generating it with the width and height, we're just assuming that it's going to be a frame buffer. Now, if we ever end up using this texture initializer with something else, we probably will want to set these parameters for what to do in terms of scaling the image and everything. But we'll come to that bridge when we get there. Now, let's go back to our frame buffer. So we'll go back into here. Now this works. We don't get any errors. And so what we'll say is GL frame buffer texture 2D. And so what this says is, hey, we want to attach a 2D texture to our GL frame buffer is the type. And then you'll notice the next thing says attachment. And so what we're going to say is GL color attachment 0. So basically we're attaching a color field to our frame buffer. So we're saying, hey, put all the colors you get into this attachment. And notice it's 0. You can actually have 1, 2, 3 color attachments, which is useful if you want to store different sort of data. You can use this to do things like post-processing effects like blurring and shadow maps and all sorts of stuff. But we're just using it for our colors. Next thing it asks for is the texture target. This is a GL texture 2D. And then it asks us for the texture, which we just created. It's this.texture.getID. And then the level we're going to say is 0. And I'm not actually quite sure what the level is. I can't remember off the top of my head, but we can look at the documentation at some future point to find out exactly what this is. Okay, but basically what this does is it creates a frame buffer for a 2D texture and attaches it to our 0th color attachment. And it uses our texture ID for the data that it's going to store. So it's going to use our texture ID to place all this data. Okay, next we're going to create that render buffer, like I said. And this is going to store the depth info. And I was wrong. I said the render buffer stores things like the color data. What I meant was the depth data. So we're going to store all of our depth data in here. You could do depth centil, but we're just going to do depth. And so we'll say int RBOID equals GL gen render buffers. So instead we're doing a render buffer instead of a frame buffer this time. Next we'll say GL bind render buffer. GL render buffer is the type we're binding, and then we will give it our RBO ID. Then we'll say GL render buffer storage is GL render buffer. What type of storage are we having? We want GL depth component, and these are not capitalized, GL depth component 32. And this is where we're basically telling it we want 32 bits for our depth component. We don't care about the stencil, we're just doing depth. And then we need the width and the height. And I'm not sure why this is not... Oh, I did the capital B here again. There we go. Now it'll recognize it. So you see then it asks for the width and the height, which we'll just pass in as our width and height that we got passed in as our parameter. Okay. Then we also need to attach this to our frame buffer. So we just created a render buffer object, but our frame buffer still doesn't actually know about it. So we need to say GL frame buffer render buffer, and we say GL frame buffer. So this is getting attached to our frame buffer. We want to attach a depth attachment, and this is of type render buffer. That's what we're using. If we look at the last one, it asks for the render buffer, which is just our RBO ID. And so what this does is it actually attaches this render buffer to our frame buffer so that our frame buffer knows about it and can use it. Then we want to check and see if this all succeeded. So we'll say if GL check frame buffer status, and we're going to say GL frame buffer is the type we're checking for, does not equal GL frame buffer complete. Then we'll say assert false error frame buffer is not complete. And what this does is it basically just checks and see if everything succeeded. If we messed something up, perhaps we gave it a bad texture, or maybe we gave it bad info, like it can't actually do 32-bit and we gave it too many attachments, anything of that sort. This will basically check and see we did everything correctly. If we didn't, it's going to give us this error, and then we can debug further to see what we did wrong. Then what we'll do is we'll say GL bind frame buffer, GL frame buffer 0. And so this is something I didn't talk about, but every time you bind to a frame buffer, every render call from this point on will go to this frame buffer. It will store the data in that frame buffer. And so if you want to start displaying it to your window again, what you do is you just bind frame buffer 0, which unbinds the current frame buffer, and then it starts putting everything back onto the window. Okay, but that's good enough for now. Let's create a couple of getters and setters. I'll actually just go up here and hit code, generate, and just do getter and setter, and then we'll just do it for both of these. And actually, instead of getting the texture, I'm just going to say int get texture ID, and then we're just going to return texture dot get ID, because that's a little bit easier, and we don't actually need to set the texture or set the FBO. Okay, so that should be all we need. We can get the FBO ID, we can get the texture ID now, and we can actually use this thing. Now let's go into our window, which is doing our rendering. It's sort of doing the main bit of rendering. So if we go up to Jade and we open up window, what we're going to do is, just so that we can see how this works, we're going to go up to the top and we're going to say private frame buffer, and we're going to get ourselves a frame buffer object. And so what we're going to do right here is we're just going to say this.frameBuffer equals a new frame buffer. And I'm going to pass it 3840 by 2160, which is the size of my screen. You should pass it whatever the size of your screen is. So if you're on 1920 by 1080, pass it that, or just whatever it is. In the future, we'll change this so that it actually queries for the monitor's real size, and then we'll just use whatever our query gets. Okay, so then this creates the frame buffer, and let's actually go back into our frame buffer and create just a couple more methods. We'll say public void bind, and this will bind our frame buffer. The way we do that is just by doing this right here. So we'll just call GL bind frame buffer, blah, blah, blah. And then we'll go over here and we'll say public void unbind. And that is this call right here where we just bind 0. Okay, some helper functions to make our lives just a little bit easier. Then when we're drawing our window, what we're going to do is we're going to say for our current scene, we'll go into here and we'll say this.frameBuffer.bind, and then we'll go down here and we'll say this.frameBuffer.unbind. What is this going to do? This is going to do it so that our frame buffer is bound when we're drawing all of our scene data. Then once ImGui is rendering, what it's going to do is it's going to render ImGui to the window. So what should happen is we should just see ImGui stuff and we won't actually see our scene. So let's hit Shift F10, see if this all works. All right, and that works just as you would expect. So we see that we get all of our ImGui data, but we don't get our scene. So if I unbind this, if I don't bind, we can leave the unbind call. It's not actually going to do anything. You'll notice we get this, and we get some problems with our textures. And this problem, once again, is happening because of the way we're saving our textures currently. We really have to fix that. I think we're going to do that next because it's saving the texture ID instead of the texture path. And so what's happening is if we take a look, what our texture ID is, it's going to be this new frame buffers ID. So if we actually remove this creation of the frame buffer, we'll see that our textures are back. But we can't do that unless we comment out this line as well. So we're not calling a null frame buffer. But yeah, what we'll see is that our textures are back, and the reason they were gone in the first place is because now when we create this, it creates a texture that uses the ID that we were using for our textures in there. And it just doesn't work right. Doesn't look right, but it is all working properly, and we can tell that because when we bind it, we see our stuff, and when we unbind it, we do not see it, which preferably means that it's rendering to some off-screen buffer that we can then use. So the way that you could see that this is actually working is you could create a quad and render our texture to that quad and see if you see our scene. Of course, the scene is going to look like black squares instead of actual textures because of our saving issues. But if you do see this on your quad, wherever you place your quad, then you'll know that this is working. We're going to do that in the next tutorial, and we're going to fix the texture saving issue, and then we're going to do the frame buffer thing. But yeah, this has been Frame Buffers. I hope you guys enjoyed it. If you did, please hit like and subscribe, and stay tuned for the next episode when we start talking a little bit more about how we can use this frame buffer for more stuff than just rendering to it, and how we can fix this texture problem where we're not actually saving the correct data. In this episode, we are going to be doing this, which is getting docking integrated. So the ImGui branch we're using, spare ImGui, now has docking enabled, and we're going to add it to our project because we can. You'll notice that I don't have the game viewport. You can actually sort of see it behind here. And so that's the whole reason we have frame buffers, because what we're going to be doing is this will become the game viewport, and we will use frame buffers to allow it to be able to be displayed as a texture within this ImGui window, within a new ImGui window. We'll see if we have time at the end of this tutorial to go ahead and do that, but if not, this is what we will get to for sure. Now, before we do start doing that, let's go ahead and fix up a few problems that we have that should have been fixed a while ago. So first, we'll go into Level Editor Scene, and up here, we just set the active game object to the 0th game object, but we should check and see if GameObjects.size is greater than 0 before we do that, because if not, you will get an error here. So this just corrects that. It's really simple, but it's good to have because you don't want to be getting random errors all the time. Next, we have this to-do that's been here forever. Let's actually fix it. And it's not that hard to fix too, so I don't know why I didn't do this sooner, but let's just go into texture. If you hit Control-N too, by the way, you can just start typing and get to the class you're looking for. Let's remove this, and let's mark text ID as transient, which means we do not want to serialize the texture ID because that is dynamic. It changes from restart to restart, whereas the file path will stay the same every time. And that's the way we want it. So now that we have that marked as transient, we need to go into our sprite render and add a new method in here so that we can set the texture to what it should be. So we'll say public void set texture, and this will take in a texture object. Then we'll just say this .sprite.set texture. All right, and now if we go into level editor scene, we can actually hook all this up. So basically what's going to happen is we're going to load all of our resources, okay? And if you remember, I had to do this to refresh myself too, so don't feel bad if you don't remember. I am opening up our text file real quick that contains our level data. So if we go into here and check out the level.txt, which at the moment is currently empty for me. Let's see if I can add some stuff real quick so that we can see something. All right, so I'll drag a few things in here with some different textures just so that we can see. I mean, technically they're all the same texture. It's different texture coordinates and stuff. But now that we have some things in the scene, if we check this, you'll see that we have components and we have the sprite render. Then we store the texture, which has the file path and the text chords. But remember, this is storing a texture object, a unique texture object for each one, because once we deserialize this, it creates unique texture objects. But our asset management system, if we look at this, the asset pool, we're actually doing it so that we only have one texture loaded in memory at any given time, and we just share that texture among our whole world. And so this becomes a problem because once we deserialize it, we get several textures, whereas we should only have one. So to fix this, what we do is as soon as it deserializes, we get a bunch of texture objects, and then we go into our level editor scene, and we have loaded everything by the time that we load the resources, because that happens somewhere up here. So we go down here and we say, okay, let's load all the resources. Then we'll go through each game object. And then if the game object has a sprite render, and if that sprite render has a texture, so we'll say sprite render spr equals g.getComponent sprite render if spr.getTexture does not equal null. So this means it did have a texture object and it just got loaded. What we're going to do is we're going to say spr.setTexture assetPool.getTexture, and then we're going to say spr.getFilePath, which we do not have. No, we do have this. It's just spr.getTexture, not text chords, texture, .getFilePath. Okay, there we go. So what this does is we go through each game object. They each have a unique texture. And then what we say is, okay, now set that texture to the one texture that they should have from the asset pool. So then it grabs the asset pool's container. Their textures get set to null. Java garbage collects it all. They get rid of all that stuff. Then we end up only having one texture in memory at any given time, which fixes our problem of having issues when it came to saving the texture IDs. So now, if we go into our window class, we can see if we turn the frame buffer back on, that, or wait, no, the frame buffer has been on. Okay, yeah, so if we just load this back in, we shouldn't get any black textures anymore, yeah. So this is all working good, and then if we go into level editor scene, just to show you that this would be black if we didn't have this, if we remove this line, and then we go back in, we get black textures. So this fixes that problem just because now they're getting set according to their file paths and not according to the texture IDs, which is what it should be doing. All right. So that fixes the texture problem. Now let's add some docking support. What I'm going to be referencing is actually from the C++ version, because the ImGui port was just like, check the C++ version's documentation. So basically that's what we're doing. And if we go into the branches, just in case you want to like see what he did, what Okernut did, you can come here. And then we're going to go to docking, which is the branch. And then you can go into ImGui demo.cpp. And once this big file loads up, you can go down here, and I usually just do Control F and then say docking, because, yep, and then you see this says show example doc space. So what I do is I copy that function because that's the one we're looking for, and we'll go down, and this is what I will be following. So I've stripped a lot of this out because we just don't need a lot of it. So we just sort of have the bare essentials of what I'm going to be doing, but this is exactly what I'm going to be following if you want to actually check it out yourself and see a little bit more detail what Okernut did in his version. All right, but that's enough about that. Okay, so to get this up and running, first of all, what we have to do is go into our build.gradle, and we have to change this version. So actually, I probably should have left this up. If we look up spare ImGui, which is the version I'm using, and by the way too, he has added Maven support. Yep, Maven support and rawjar support. So that's good if you want to use either of those methods. But if we go into here, you'll notice that he is now using version 1.77-0.17.1. So we'll copy all of that. And then actually, if you just look at the Gradle build too, you'll see it says it right here. So we'll copy that, go into here, and then we'll paste it right here instead. So now we have the correct version. Let's import those changes by clicking down there. Gradle will import it. And by the way, if you accidentally exit out of that too, I can't see it right here because of the way I have this in presentation mode, but you should see a little Gradle build thing up here, and then you can click on that and then click import or refresh or something, and it should import it. Okay, so now that we have that, we do have the project. So let's go ahead and implement docking. Go into ImGui layer, because this is where we have all of this stuff happen. And what we're going to do, first of all, because this happens, I forgot about this too. It looks like he might have changed some of these, the naming. So instead of, you're going to have a lot of errors. So just hit Control or Alt Enter, and then hit Import Class. That should fix that. And then hit Alt Enter, Import Class. That should fix that. Alt Enter, Import. Alt Enter, Import. And then once you get a few of these done, it should fix itself. And then we'll hit Alt Enter, Import. And then I'm going to go up here. If you just remove all these, it'll import the rest. And you should be good. So now this is working fine again. If you run it, it should still run the same as we just had it a minute ago. And you see that it does, so that's good. Next, what we want to do is every frame, we are going to have to start our dock space. So we're going to write a new function right here, and we'll just call this setup dock space. And that will set up our dock space for us. And inside of here, we will sort of do all of what we need to have done. So let's scroll down to the bottom, and we'll say private void setup dock space. And once again, this is just like the show example dock space from ImGui. So first thing we're going to do is set the window flags to be ImGui window flags menu bar, so it always has a menu bar, or ImGui window flags no docking. So this is sort of the parent window, and it's a little bit weird. I'll show you exactly why we have this one as no docking, and then there's like another window that is the docking window. And this will make sense once we actually do this in just a second. Okay, then we're going to say ImGui.set next window pose 0.0f 0.0f ImGui cond.always. So this will always be the entire window's size. So what we're doing is we're saying make sure it starts at the top left of the window, and it is the window's width and the window's height. And we'll say ImGui.set next window size. And like, window is obviously an overloaded term here. So when I say the window as in our main window, and then this is like the main window of ImGui. So yeah, it can get a little confusing. So then if we do that, we should be good. Now the main ImGui window will take up the main size of the window of our application. And then we'll say ImGui.push style var. So this is just a style variable, and we'll say ImGui style var window rounding is 0.0f, and I will change this to ImGui. I'm just going to duplicate that, and then we also need to set window border size to 0. Then we need a few more window flags, so we'll say window flags or equals bitwise or ImGui window flags dot no title bar, or ImGui window flags dot no collapse, so you can't collapse it, it has no title bar. ImGui window flags dot, and I'm gonna move this to the new line because that's easier, no resize, or ImGui window flags dot no move, not no mouse input but no move, or, and then we'll go to another new line, we'll say ImGui window flags dot no bring to front on focus, or ImGui window flags dot no nav focus. And what these last two do is this just makes sure it's always behind everything, since this is like the main window we dock into, sort of. And then this just makes sure that when you click it, it doesn't actually focus on it because it's not a focusable window. It's just sort of there. So that should be all the window flags we need. Okay, next we'll actually create the window. So we'll say ImGui.begin dock space demo, and then we can call this something different if you want. And we're going to pass in a new ImBoolean true. This is always going to be true. We don't care. They're not going to be able to close it, so it doesn't matter. And we're passing the window flags because we have it as no collapsible right here. So this means that even if they were to press the X button or whatever, it wouldn't actually close this main window. Now we're going to say ImGui.pop style var, since we already used those styles. 2, we need to pop 2 since we pushed 2 right here. We pushed 2 on the stack, we popped 2 off. Then we have one more thing, which is the dock space. But I'm not going to do the dock space immediately because I want to show you what happens if you don't. So one last thing we have to do, we began a window, that means we have to end a window, because if we don't, if we run this, you're going to see you get this weird error which says g.current stack size equals 1. And then it actually gives you a helpful hint. It says mismatch begin child versus end child. Did you forget to call end or end child? And we did, right? Because we have this imgui.begin right here, but we don't have the end. Thing is, we want to end it after we've done all of our other ImGui stuff. So you see we set up the dock space, we current scene ImGui, then we show the demo window. Before we render, we just need to make sure that we end. So we'll say ImGui.end here. Preferably I would do it in end frame, but that's after we render. We have to make sure we do this before we render, so we might change this up in the future, but for now that works. So now, if we run this, we're going to get one big window in the back. So you see we got one big window with a title bar, but there's a problem. What happens if I try and dock this? I can't dock it into that window, which is kind of weird. Oh no, I forgot some other stuff. Okay. I was about to show you what happens, and it doesn't even work because we never actually enabled docking. We have to go all the way up to the top first. So when we're initializing ImGui, okay, right up here. So when we're setting all the flags and stuff up here on line 30, we need to make sure that we set up the config flags for docking to be enabled. So we'll say set the docking enable flag. That way we actually have docking enabled. There we go. Now if we go, you can see that I can dock into other windows, but I can't dock into this window. And it's like, okay, why is that not working? And remember, it's because we put this flag down here. We said no docking, right? Okay, well, let's just comment that out, right? We want to be able to dock into the main window, right? But then you get this problem. If I do this, it takes up the whole screen size. That's not cool. And then you gotta do weird stuff to get it small enough again. And that's annoying. And no matter what you do, you'll see that you have this problem every time. So that's because you didn't actually set up docking correctly. What you're supposed to do is do this no docking thing, and then you set up this thing called the dock space. And so when you go down here, you say imgui.setup.dockspace. Okay, so you say imgui.dockspace, and then we're going to say imgui.getID dock space. All this does is it's just a hash function, so it's just hashing this into some string or some number, and then we just set the dock space's ID as that number. So this will enable our docking, and actually can't go quite yet. Okay, yeah, that is unchecked. So make sure that's no docking, and then we set up the dock space. Now we can go up here, and you'll notice it only takes up half the size, like only a little bit, the normal size of the window. And so that's just sort of ImGui's way how it works. But now you see we can actually move things around, and we have docking working properly. But like I said before, there's a problem. You can't see your game anymore. You can sort of see it here in the back, but we want it to be right here, right? And so that's where frame buffers come in. But we are running out of time. So in the next episode, what we're going to be doing is we're going to be setting up an extra window here where we will render everything into our frame buffer. Then we'll draw that texture. So the frame buffer is just a texture, remember? And we'll draw that texture plastered across this screen as big as we can. And that way we have some access to a game viewport. That will bring in some new problems, though, that we will take a look at then. I do want to mention one more thing. I've been hesitant on how much I should do in this Java version because I think that if you're going to do a full game engine, you should do it in C++. Typically, I would say if you want to make a game, make it in whatever language you want because it really doesn't matter. But C++ does give you more control over some things that are kind of important, and it can let you access more speed when you need it, which is kind of important for a game engine. So I don't know how far we're going to take this Java version, but I definitely want to eventually start in the future a C++ version tutorial which isn't that bad. I promise I've been doing it. It may seem daunting, but C++ ends up giving you more speed in the long run, and it gives you more flexibility to do other things. It just makes some things easier. For example, scripting languages. So we'll see how far we take this. We may just take it till we complete Mario and stuff and have a basic engine. You guys can extend it if you want to, more in Java. But yeah, we'll see about that. And one last thing I want to mention too is I start my new job next week. So I am going to have a lot less free time. That means I don't know if I'll be able to do 2 tutorials a week. I'm going to try. I'll see how it goes next week. I'm going to try and do 2 tutorials, but I might just be so burnt out from my job and stuff that I can only get 1 in a week. So it may be, we may have less time to do these, because I also want to work on my game engine, the things that I'm working on personally and stuff too. We'll see how that goes too and stuff. I'm hoping that I'll still have enough energy to do 2 tutorials and work on my game engine and do my job. In this episode, what we're going to be doing is rendering our game viewport to an actual viewport. So you should be seeing what that looks like right now on the screen. And basically, we're just going to be making it so that whatever you want to render your scene to will be displayed in a frame buffer texture. And that will just be rendered into an image that ImGui will display on one of its panels. Now, this image will be set to a target aspect ratio, so that if you are targeting specific aspect ratios, you can see what your game will look like on those aspect ratios inside of the viewport. Now, how does this all work? Real quick before we start to, just notice this buttery smooth recording in the 4K. So one of the viewers mentioned a new recording software for screen capture called Streamlabs OBS. I was using OBS previously. I don't know if it's a difference or if it's just because I upgraded it to 4K and 60 hertz recording frame rate, but it just looks so much better. Anyways, moving on with the episode. What we have here is just sort of a representation of what you saw in that preview before. We have the main window, which is out here, and then I'm just stripping it down to the bare essentials, which is the game viewport, which I will just do GV, which is right here. These are the things we care about. Now, there's a couple things that we have to note, because this game viewport right now may be 800 by 600, but this size can definitely change. It is not going to be like this, and clearly this is not to scale, because this is way more rectangular than an 800 by 600 ratio would be, but it will help us illustrate a point. So what we want to be able to do is say, okay, so if our panel has an overall width and height of 800 pixels by 600 pixels, and our target aspect ratio, which we'll just call TA right here, is 1920 by 1080, or you could just say that's 16:9, so an HD target aspect ratio. If we are targeting this aspect ratio, where do we place the picture inside of this square? As you notice, we had those black bars, and the reason we had the black bars is because we want our game to maintain an aspect. So what we actually have to do is there's 2 methods you could go, right? You could either stretch it out, drag it so that it's bigger, and then it would be like over your picture, but then you're losing information. And while you're editing your game, you don't want to stretch it. Maybe in production, that's what you would want to happen. You don't want these black bars, and so that's definitely something we can add support for, so that they do lose a little bit of information. But while you're editing it, you want to be able to see everything. And so instead what we want to do is we want to just have these black bars on the sides so that we can see the whole game scene as it would be from the camera's perspective that's actually in the game world. So we have to figure out, okay, where's the top left corner? Where do I place this game? And what is the width and height inside of here? So what is this width and what is this height, so that we know what to tell ImGui, so that ImGui can display the properly sized image and panel inside of our game. Now, all that stuff is not very complicated, okay? So what we do is we'll just label these X, Y, and now it's literally just a geometry problem, right? So ratio is just width over height. So width, if we look at this equation, is just ratio times height. And height is just, if we multiply this, divide this down, just width over ratio, okay? So that's what our X and Y is, right? So this is X, this is Y. That's what we want to solve for. Now, what we can do is, like I said, we can do a little shortcut. So what we'll do instead is we'll just say, okay, let's pretend the width is actually this width. We'll say width equals 800. Okay, what would the height be if we had this width? So then what we would do is we would just plug it in with the R that we want. So we would say, okay, so the R that we want is actually 16 to 9. We don't want 4 to 3. So what we do is we just say, okay, plug in 16 to 9 for R, and then plug in 800 for the width, and that will give us some number. And this number will end up being bigger than 600. It's going to be like some number greater than 600. And so what this is going to tell us is it's going to say, hey, if we try and stretch it, if we try and stretch this image the entire width of this, what we're going to end up with is it's going to be too big. It's going to not fit in there. And so we'll say, oh, okay, well, we can't fit it in the horizontally. So instead, we'll do it vertically. So then we'll say, okay, let's set the height equal to 600 because that's the maximum height we can fit. And then what would the width be? Well, the width would just be, let's plug in our target ratio, which is 16 to 9. And then 16 to 9 times height, which is 600. And that will give us some number that is less than 800. Then this would tell us, okay, so now if we make it the full height, we will get some width that is less than 800, but that tells us that we have the appropriate width and that we can fit everything into the game viewport. So this is the first step. We just solve for the width and the height, and we just try the width first. If that fits, then we'll just use whatever we get with our calculations. If it doesn't, then we use the height, and then we calculate the width. Now, after we do that, we have to figure out where to place this top left corner, which is very simple once we get the width, because we know what the center is. The center is just 800 divided by 2, which would be 400, and 600 divided by 2, which is 300, right? So that's not too bad. Now we need to calculate what that top left corner is. Well, we know what x is because we just solved for that. So then to get that top left corner, we would just do center minus, and I'm going to do vector notation, x, y over 2. So all that means is whatever x is, let's take in half of that, which would be this length. So if we do 400, which is right here, minus this length, that will get us this x, which that's the right x. And then if we cut the y in half, 300, and we just do, okay, take 300 minus this length, then that will get us right down to here, which is what we want, right? And we could just flip it. So if we had to, we could flip the 300 and the 400. It wouldn't matter. And you'll see what I mean once we actually get into the code and everything. But basically, this is just a very simple solution, just finding where to place something centered, right? You just take the center of the big thing you want, and then you subtract half of the size of the thing you want, and that will give you the position that you want to place it. Okay, so hopefully that made some sense. Let's go ahead and code this real quick and just get it done. All right, so I am just back inside of our project, and if I start it up, we can refresh ourselves. We got the dock space up and running last time, and you can see that right now we would like to have our game viewport be in a little panel down here, just like we saw in the preview. So how do we do that? Well, let's go up into our package. First of all, create a new package, and we're going to call this editor. This is going to be where all of our editor components live, okay? Ideally, it would be separated entirely from our engine, okay? But I'm not doing that because it's a little bit weirder to do in Java than I know. So it's a lot easier to separate this out in C++ with libraries, which you could clearly do in Java too. I'm just not that familiar with doing this type of stuff in Java, and I eventually want to move this series to C++ anyways. So we're going to do it in a way that works, not necessarily the best way. So ideally, this would be in a completely different library than our engine. Anyways, so we'll create this new package to separate it as much as we can. And we're going to go in here and create a new class. We're going to call this game view window. And this is going to be the window that contains our game view. Now, this is going to be a completely static class, and we're going to have an ImGui function in it, and then some private helper functions, which we'll get to in just a moment. So this is the way I like to do my editor panels. It's just static classes that have an ImGui function because they don't really contain anything. They're just containers, right? They don't really act on any sort of data. There's no reason to have an object. You could, because technically this could be an object, but it's just one thing, right? There's only ever going to be one of these objects. So having it completely static, I think, is fine too. But better practices would be to just have a single object inside of your ImGui layer, which we'll see what I mean in just a second too. Anyways, though, what do we want to happen when we do this? Well, we just talked about it. We want to be able to draw the ImGui window, right? And how do we do that? Well, let's just go ahead and we'll say ImGui.begin, and we'll say game viewport. And we're going to say we do not want this to have a scroll bar because they shouldn't be scrolling in this. And I'm going to do an or symbol and say or ImGui window flags dot no mouse input, no scroll with mouse. So that if they do the scroll wheel, it's not going to try and scroll the window. So we'll just take those two out. And then what we would like to do is say ImVec2 window size. So this is going to be the size of our panel inside of it. So this is going to be the size of the game viewport, is get largest size for viewport, which is a function that does not exist, but we will create. And then we're going to say ImVec2 window pose. So this is where it's going to be centered inside of our panel. And this is going to be get centered position for viewport. Really clear function names. There's no debate about what those do and makes it nice and easy to read through this. Then we're going to say ImGui.set cursor pose. And we're going to set the cursor pose to window pose.x, window pose.y. And what this does in ImGui is it basically says, okay, I'm going to set so that the next thing, which in our case is going to be the picture that represents our game scene, that I'm going to place into this window is going to go at this position. So we're basically just saying draw the next thing at this position. Then we're going to get the texture ID for our frame buffer. So we'll say texture ID equals window.get frame buffer, which we don't have, but we will, and then .get texture ID. And I'm going to hit Alt-Enter and import that from Jade. And then lastly, what we're going to do is we're just going to say ImGui.image, texture ID, window size.x, window size.y, 0, 1, and 1, 0. What this does is, if we look at the parameters, it just says, okay, so the texture ID, well, we got the texture ID. That's self-explanatory. Size X, size Y. How big is this image that we're doing in this ImGui window going to be? Well, we're making it the window size X and the window size Y. And then it takes into UV0, UVX, UV0Y, UV1X, UV1Y. And that's just saying, okay, based on this texture, where do you want me to sample from that texture? And we're saying 0 to 1 and 1, 0. So the bottom right corner, no, the top left corner to the bottom right corner. And we're doing it backwards like this because otherwise it will show up upside down, and I'll show you what that means too. But basically it's just UV coordinates. There's nothing special about that. Texture coordinates, we've looked at those before. Then we'll say ImGui.end. That's all there is to it. It's really not that bad of a function. Now we need these two functions that we declared but didn't actually use. We'll say get largest size for viewport and private ImVec2 get centered position for viewport. And of course, these need to be static as well because we are calling them from a static method. Now I'm going to say you guys should try and implement these. You can see exactly what they're supposed to be. It's very self-explanatory. You know exactly what they're supposed to return. Try and implement it. You may have to look at ImGui's documentation to figure out how to implement it, but you should be able to. And a hint too, it shouldn't take you too long. Anyways, I'll implement those in a minute. For now, let's go into window and create this get frame buffer function. So I'm going to go Control N and then type in window to go to the window class. Go down here, just say public static frame buffer get frame buffer. And I'm going to say return get dot frame buffer. And I'm going to do one more over here, say public static void or float get target aspect ratio, and this will get the target aspect ratio for our game. And I'm just going to say return 16.0f over 9.0f. And hard code it in, we can get this to actually get the monitor's aspect ratio in the future. But for now, this should be fine. If we go back into our game view window, we lose this error now, and now we just have to implement these. So let's implement the largest size for the viewport first, because this one's a little bit easier. So what we want to do is say ImVec2 window size equals new ImVec2. This is going to be the size of the red rectangle in our illustration, the larger rectangle that contains the smaller rectangle, which is the actual game viewport. Then we're going to say that size is ImGui.get content region available, and we're going to pass in window size. And this will just fill in window size with how much space we actually have. And then what we're going to say is window size.x minus equals ImGui.getScrollX, and window size.y minus equals ImGui.getScrollY. And the reason we're doing that is because if we actually take a look inside of here, it says this is equal to getting the content region max minus get cursor pose. So then if we take a look at what get content region max is, let's try and find out. Okay, let's just go into here. If we say ImGui.get content region max, and if I click into here, okay, here we go. So this says this gets the current boundaries, typically window boundaries, including scrolling or current column boundaries and window coordinates. Notice this key phrase, including scrolling. So in order to be super safe here, in case the window accidentally scrolls, we're subtracting out the scroll parameters because we don't care about the scroll. We just want how big we have inside of that red rectangle. All right, so now that we have the size, we're going to say, try and get the aspect width and height. So we'll say aspect width equals window size.x, and then we'll say float aspect height equals aspect width over window.get target aspect ratio, right? We're just plugging in those equations we talked about. And we'll say if aspect height is greater than window size.y, so if it's greater than the amount of space we actually have, then we must switch to pillar box mode, which basically just means we have the black bars on the left and right side. So we'll say aspect height equals, and then we'll say window size.y, and then we'll say aspect width equals aspect height times window dot get target aspect ratio. And this will literally just plugging in those equations. And I totally did not type that right. So let's see if I can rename this real quick. Aspect height. Okay, there we go. Now we have that done, and all we have to do is say return new ImVec2 aspect width and aspect height. This does exactly what we want to do. It gets the largest size that we can fit the viewport into. Okay, then for the centered viewport, what we're going to do is we're actually going to take in an ImVec2 aspect size. So this was a little misleading. I should have put this in there too before telling you guys to try it, but we do need to add in the window size, and that will just help us that we can center it appropriately within the full window. So then we'll say in here, ImVec2 window size. Once again, this is the red area, so the overall window size, and we'll do the same thing, get content region available, window size, and if we pulled all this out into this function, we could reduce that duplication, but I like having these in their own functions better because it's a little bit more readable. And we'll do this again one more time. Technically, we could make a function to do that and save a little bit of time, but it's fine. Then we're going to say float viewport x, so where is the x position centered? And we're going to say that is window size.x over 2.0f, so over the center x minus aspect size.x over 2.0f. And we'll do the same thing for viewport y. Window size.y over 2 minus aspect size.y over 2. And then we'll just return a new ImVec2 viewport x, viewport y. And we're going to have to do one more thing, which I will show you in just a minute, but we'll leave it at this. And so this is just doing exactly what we talked about. Once again, it's just taking the center x, subtracting half the size of the smaller rectangle that we can fit inside, and same thing with the y's, which gets us the appropriate x and y. And that is it. Our function is done. Real quickly, though, we're going to notice that we have a problem when we try and do this. Well, first of all, we're not even calling it, so it's not going to do anything. But if we go into our window, or actually let's go into our ImGui layer, and I'm going to say right after we show the demo window, what I'm going to do is say game view window dot ImGui, just so that we call ImGui right inside ImGui with everything else. Okay, so now if we do that, you notice you'll get this tiny window up here. If we pull this out and then we say put this down here, first of all, you'll notice it looks like it's growing correctly and everything, but it's all black. And you're like, okay, why is it all black? And well, that's because we didn't enable our frame buffer. So let's go into our window class, uncomment this line. Now we actually have our frame buffer being drawn to. So If we run this again, okay, it's still black. Why is it still black? That doesn't look right. And the reason it's still black is because if we go into frame buffer, so I'm going to Control N frame buffer, you'll notice that we create a new texture for it right here, right? Okay, if we go into texture, we never define what to do with the texture if it's bigger or smaller than what it should be. So this was a problem that I ran into a while ago, and it took me forever to figure out why I wasn't seeing anything on my frame buffer. And basically, if you don't define what should happen when you have your min filter or your mag filter, it doesn't do anything. And if you remember, the min filter and the mag filter are literally just what to do if your image is stretching or if it is shrinking. And so if we say linear, then this will make it so that it blurs it as it stretches and shrinks. And then if we said closest, that would pixelate our values as we stretched and shrunk. And there you go. It looks sort of right. We get a black screen with our lines. And the reason we're getting the black screen, if we go back into our window, you'll notice that we don't bind our frame buffer. You'll notice we bind our frame buffer after we clear color, when we really should bind our frame buffer before we do clear color. That way we make sure to get our clear color in there. And then it is now a white screen. And if we move our stuff around, it all works properly. What you'll notice though is that this does not look right, right? We have this little space up here, first of all. And second of all, we have a space down here. The reason for this space is because we're not taking into account this title bar. And so the way we can take into account that title bar is if we just go into the game view window, right here when we're getting the centered position, we should just add in ImGui.getCursorPoseX and plus ImGui.getCursorPoseY. And that will just make sure that we take into account that title bar height. But that doesn't explain why we get this thing. And the reason we're getting this white space is because we are never calling GL viewport. And what basically GL viewport does is it defines the maximum size you're going to draw to. And so the space we're drawing to is that frame buffer. And if we look at the frame buffer, we can see that when we create the frame buffer in the window, we see create a new frame buffer of size 3840 by 2160. And basically what that means is we would also need to make sure that we're drawing to a size of 3840 by 2160. So if we call GL viewport and we pass in 0, 0, and then the width and the height, then we should see that problem disappear as well. And there we go. Now we get it drawn perfectly as it should, and there's no weird errors. Last thing you're going to notice, first of all, we can't click onto this. That's because this window is consuming the click events. We'll have to fix that. Second of all, why is the block way off from my mouse? And notice how it gets closer as I get closer down there. That does not look right. The reason for that is because now that our game viewport is sort of sitting in here, I don't know how it just changed up everything too. But now that our game viewport is sitting inside of here, we actually have the wrong mouse coordinates, right? Because right now we're calculating the mouse coordinates in this entire window, which is this entire thing, the entire size. But really what we need to do is calculate it as if the window started here and ended here, if the mouse is inside here. It's kind of confusing, but we'll talk about this in more depth in the next tutorial. In this episode, what we're going to be doing is what you should see on the screen right now. We're converting our mouse screen to proper world coordinates in this episode. And we've done this before, which you should recognize this because this is from the first episode, which check the top right corner and click on that link if you haven't seen that. This is how we did it in the beginning when the world took up the entire window's width. And we're still going to be using the same technique, but we have a problem because now we have a game viewport that is somewhere inside of this overall window. And so we can use the same technique we used here. What we just have to do is we have to convert first from our mouse position, which could be like anywhere on this entire window, into a relative coordinate to this. So basically, if the mouse position was here, what we would want it to say is, okay, it's this many pixels from this corner, instead of saying it's this many pixels from this corner. And the way you do that is very simply, you just subtract this mouse screen position from the bottom left or top left corner, whichever way you're coordinated. So if we subtract this minus this, what we'll end up with is this vector right here, which is the one we want. And then we can continue with the rest of the calculations the exact same way that we did before, and everything should work just fine. And then we'll have to do one other thing, which is ImGui currently wants to capture mouse coordinates or capture mouse inputs if we click onto the ImGui window, which is here. So every time we click onto this window, it doesn't do anything because ImGui is capturing that event and we're not passing it through to our application. So what we need to say is if the mouse is anywhere outside of this, then let ImGui do with it what ImGui wants. But if it is inside of it, we want to capture the mouse event because this is something we care about. So very brief preface to this episode. Now let's get started. All we have to do is subtract this corner and capture those mouse events appropriately. So let's see how we do that. All right, so I have my game window open here just to accentuate exactly what I'm talking about. If you'll notice, when I move the mouse, the object is not tracking the mouse properly, and that's because we're not calculating world coordinates as if the world started here. Instead, we're calculating them as if the world started here. And so you'll notice when I go up to this top left corner, the game object actually is in the top left corner of the world. And if I go to the bottom right corner, it's in the bottom right corner, which is what we would expect. So now we just need to say, okay, just act like it's starting from here instead and ending here, which is what we will do. So in order to do this, we need to go into our mouse listener because this is where the magic happens. I'm going to take these two functions, which are the important ones, and I'm going to copy them and paste them down here below get mouse button down or whatever. And then we're going to have to create some new variables to help us out. So we just need a couple of vector2fs. We'll do private vector2f, and this will be game viewport pose. And we'll just set that to a new vector2f. And then we'll say private vector2f game viewport size. And that's also a new vector2f. And this will just help us. I also don't really like the way that this works. Ideally, we would have a different method for doing this. I'll show you just the method that I'm using right now, and then you guys can let me know in the comments if you can think of a better solution to do this. Okay, and we're going to create two setters for these two. And if we go back down here, we'll just modify this a little bit. Instead of doing the equals there, we'll just say dot set, and then we will change that right there. And we'll go over here, we'll say dot set instead. And Alt-Enter on the variable name to pull up that menu to select, create the setter for it. Okay, so right now what we're going to be doing is we're going to be manually setting the game viewport's position and size. So inside of our game, that would be this top left corner would be the viewport position. The top left or the bottom left corner. I can't remember what Y coordinates we're using for reference. But it'll be the position, and then the size will be the size of this rectangle right here. And so I don't like the way that this works once again. I think there is probably a better solution, but this is what I've used, and I just have been too lazy to fix it. So I'll show you how to use this method to get it done, but there's probably a better method. Okay, and so we can literally use almost this exact same method, right? Except instead of doing this, what we want to do is we just want it to be relative to the game viewport. So instead of doing this, what we'll do is we'll just say minus get.gameViewportPose.x, and then we will say over, instead of the Windows width, we'll say get.gameViewportSize.x. So the game viewport is our frame of reference now, and we'll just do that, which should get us the correct results. And then we'll go down here and we will do the same thing. Instead of window.getHeight minus getY, we'll take that out and we will do minus get.gameViewportPose.y, and we may have to change this. And then we'll do divided by the get.gameViewportSize.y. Okay. And one other thing, this class is completely static, so I'm not sure why I made it a singleton. You could probably get rid of these gets and just make these all static variables, but I don't feel like changing that right now. So that's some other things that you could do to improve just getting things and stuff, because this is kind of annoying and it's not really necessary. Okay, but that should be all we need to do. And then everything else should work the same way. Now, the only thing that I'm worried about is when I was testing this earlier, when we do get inverse projection dot multiply, what this does is it actually creates a, it modifies the actual inverse projection matrix. And so I'm going to change this up a little bit because I'm not sure if this will mess things up, but we'll go into here and we'll just say matrix 4F. This is going to be our view projection. And then I'm going to go into here and I'm just going to say that the view projection is equal to the window dot get scene. Well, yeah, window dot get scene dot camera dot get inverse view. I'm not sure why I did projection view here too. So yeah, we should do view times projection. And then we'll say dot multiply window dot get scene dot camera dot get inverse projection. And then we'll do a comma there. And if you do the parameters, you'll notice that this is destination. And we'll say destination is view projection. And this is definitely hard to see. So I am going to do a couple things to make this easier. First of all, let's just get the camera. We'll say camera equals window dot get scene dot camera. And then we can remove all of this with camera. And we can remove all of this with camera. And we'll just initialize view projection here. Okay, there we go. So now we get the camera, we get the view projection just by multiplying the camera's inverse view times the inverse projection. And then inside of here, we will do temp.multiply that view projection. All right, and so when you do the multiply on the matrix like this, what it does is it places the result of this multiplication into this matrix, which is what we want. And then I'm just going to copy all this. And we will just paste it right here. Like so, and that should be good. Okay, now fingers crossed, this should work properly. However, we are missing one step. We never actually set the game viewport position or size, and we do need those in order for this to work correctly. So let's go to our game view window and set those appropriately. And this is where I'm saying I don't really like the way this is working, but this is the way it's working. So we can get the game viewport position pretty easily right after we set the cursor pose right here. We're saying, hey, this is where we want to put the game viewport. What we can do is, I'll just do a few spaces. I'm going to say ImVec2 top left equals new ImVec2. I'm going to say ImGui.get cursor screen pose. And I'm going to say put it into top left. Then we'll say top left dot x minus equals ImGui.get scroll x. And top left dot y minus equals ImGui.get scroll y. And this is very similar to what we were doing down here too. We subtract the scroll x to get that out of the way. And what does get cursor screen pose do? Well, what that does, we see it says it gets the cursor position in absolute screen coordinates 0 to display size. So display size would be like the actual window size. And what this means is that when we get this cursor screen pose, this is going to be absolute in terms of our window. And that's what we want, because now that we have the top left of our game viewport in absolute screen position coordinates. It's perfect. That's what we were looking for. And then we just subtract the scroll x and scroll y to make sure we don't accidentally pick that up. Then very simply, we can just say mouse listener.set. And we don't have our setters for some reason. So let's go into mouse listener. And I thought we did, yeah, set. Oh, and these are not static. Make this static so that we can actually use these. And then we can just change that to get and change that to get. Okay. And then we'll go back into the game view pose or game view window. Now we can say mouse listener.set game viewport pose. We'll do that one first. It's a new vector 2f. Top left.x and top left.y. And then we'll go ahead and say mouse listener.set game viewport size, and that's just a new vector 2f. And we already have that. It is just window size.x and window size.y, which you'll remember we have right here get centered or get largest size for viewport, and we store that in window size. Okay, so that should be all we need. Now if we start this, fingers crossed, it should work the correct way. Okay. And it does, except you'll notice that our Y positions are flipped. So that was one thing I forgot about. ImGui has their Y coordinates flipped compared to OpenGL. So we can go into mouse listener and we can fix this very easily just by negating this current Y right here. So if we just do a negative and wrap this in parentheses, that should flip all of the Y coordinates and then we will get the appropriate positions. There we go. And now it's all working the way it should. You'll see it's a little bit off with the X position. And that looks like it might be a result of floating point precision errors. Because you'll see that it looks off here, but then the farther we go in, the more precise it gets. So I'm guessing this is floating point precision errors. It could be something else. But for the most part, it works properly. But if we click, we can't place it down anywhere. And why is that? That's because ImGui is consuming those click events. So what we can do is we can go into ImGui layer. We encountered this before too. And the way we fixed it is we said if ImGui does not want the mouse capture, then we'll call our mouse button callback. But in this case, ImGui does want it, but we still want it too. So we'll say or not, and then we'll say game view window dot get want capture mouse. So we'll use the same syntax as ImGui here. Then we'll just go into our game view window and create a method that does this. And we'll say control N, game view window. And then right here, we'll just say public static boolean get want capture mouse. And we will just return when do we want the mouse capture? We want the mouse capture whenever the mouse is inside of this little area, which is our game viewport, right? We want it when it's in here, but if it's out here, we do not want it. So we want it in here, we don't want it out here. And the way we can get this is by storing a few static variables that will help us out. So we'll just go in here and we'll say private static float left X, right X, top Y, bottom Y. And these will be the X's and Y's of our game viewport. And then we can just set those up here. We'll just say left X equals window pose.x or left X down here. Left X equals top left.x, left Y, or top Y equals top left.y, and then we'll say right X equals top left.x plus window size.x, and then we'll say bottom Y equals top left.y plus window size.y. And this should help us out because now we can go in here and we can just say return whether our mouse is within those boundaries. So we'll just say return mouse listener.get X, and this is just the screen X, and then we'll just say is greater than or equal to left X, and mouse listener.get X is less than or equal to right X, and mouse listener.get Y is greater than or equal to bottom Y, and mouse listener.get Y is less than or equal to top Y. And I believe this should be minus. We'll see. We might have to fix the Y's here, but let's see if this works. So we go into here, we click, it's not working. Okay, and I just had it flipped. So this top left is top left to ImGui, but it's actually bottom to us. So if you just make this bottom Y and then top Y is top left Y plus window size.y, then if we go back in, you should get your mouse events when you click inside. So as long as I'm in here and I click, I can place items. But if I go outside and I click, it does not place it down because I'm not inside the game viewport. Okay, so now we can actually place objects into our game world with our game viewport located as it is. And this should work if your camera starts moving too. This is good. You know, we're making progress. In the next episode, what we'll probably do is get around to making the camera move when you press the middle mouse button. Now, in this episode, what we're going to be doing is covering 3D picking. What is 3D picking? It's simply clicking on an object in your screen and returning that you clicked that object. So, in the case of a 3D world, it could be more complicated. You could have 3D objects like some tree, and the tree is coming towards the camera, but it's also going away from the camera. And if you click on this branch right here, it will return that you clicked this tree. But if you also click this branch over here, it still returns that you clicked this tree. Now, we of course have a 2D context, so we'll only have 2D objects, but we want the same idea to apply, where if you have an object here, you click on it, and it returns that you clicked object of ID blah blah blah, wherever that is the object's ID. So if that was 0, 1, 2, 3, it would return 0. Now, how do you do this? The first approach, which I thought of and implemented and realized was garbage, was it's not garbage, but it's just not the best solution. You can have bounding boxes, right? So if your objects are squares, you just put a square around it, put a square around it. Then you run a physics calculation every time the user clicks, and you go through your physics world and your game object and all that stuff, and you return which boundary the mouse clicked between. But what happens if you have something like this? You have a donut, then you have a character whose leg just so happens to go through there, and then his other leg goes through there. And what if our user clicks right here? They're not expecting to get this donut whose bounding box is going to look something like this. Well, it'd probably be a circle if it was any good, but they're not expecting it to hit this donut. They're expecting it to hit the player behind the donut. And if we click here, we're not expecting to hit the player, we're expecting to hit the donut. And so this calls for a better solution. This solution will also work with arbitrarily complex objects without any hit in performance too, because think about it, if you have an object shaped like this, doing a physics detection to check and see if it was exactly inside or outside this object is very difficult. But we don't need to do physics. Instead, what we can use is 3D picking. Now this is basically just coloring our image according to the IDs of our objects. So what that means is basically we color the background and we color it some color that's like, oh, this is our -1 color. It just means that there's nothing here. Then for each object, we would color them according to their ID. So this one would be color 1. He'd be 1s everywhere where his pixels take up. He would be 0 everywhere his pixels take up. He would be 2. And he would be 3. Just every single place. And then this guy, say he was object 4, would have 4s for every single pixel he took up. Now, is there any way that we could potentially figure out how to color every single pixel according to an object that's occupying that space? It turns out there is. It's this thing called shaders, right? We know what shaders are. We know how they basically just color something according to an object. We know we're using a batched render which patches in a bunch of data to the GPU to color each pixel on the screen. Now all we have to do is say, hey, let's do 2 passes over our game world. The first pass is going to be invisible. We'll color a window of the same size as our game world, except what we'll do is we'll color it with object IDs. Then the second pass is our render phase. Inside the render phase, we actually render everything to the screen. It's really that simple. We'll just create an invisible texture that we query every time the user clicks, and we look up the pixel they clicked on, and then look it up inside of this texture that we render to that's invisible, and then it returns us the ID because it's literally just the pixel color. And then we render again so that they can actually see their game world, and we just render the appropriate colors. Now, there's a lot that we have to do in order to get this all to work correctly, so this tutorial is going to be a little bit longer, and I apologize in advance for that, but I think it is well worth it. Now, how exactly do we accomplish this, though? Before we actually go in and start coding, I do want to briefly go over how this will work. And we'll use frame buffers, right? We used a frame buffer before, and we're using it to basically render our scene to an invisible picture that we then display to the user later on, resized, right? That's how we're putting it onto our ImGui window. Well, we'll just create another frame buffer, except this frame buffer will say we're going to have a special shader, which basically just colors IDs. Then we'll render to this frame buffer using this special shader, and we know that we can grab the texture from a frame buffer pretty easily. And so if we can grab the texture from a frame buffer, GL gives us a few functions called GL read pixels, and we can basically just query this function. And this function will say, hey, give me an XY position on the texture you want to look up. I'll return it to you in some array. And then GL read pixels returns us the pixel that we just read from this frame buffer. And now we've got the pixel that we just clicked on. With this very brief introduction, let's go in and start coding it and actually see how all this works. Now, let's just remind ourselves of where we left off in the last video. If you remember from the last video, we basically made it so that the screen coordinates are being picked up properly again, and we can calculate like the mouse coordinates inside of the game viewport according to world coordinates. That's basically what we did. Now, let's go and start to do this by going into our render package, and we will create a new class called picking texture. And this is basically going to be the picking frame buffer, picking texture, all that stuff just wrapped into one class. Now, I'm going to admit this is not the best way to go about this, and there are definitely better ways. Particularly, I don't like how this is tied directly to the engine. When are you ever going to need to tell what object ID a user is clicking on when you're not in the editor? If you know what I'm saying. Like, I think this should be an editor engine editor specific feature. This should not be part of the actual engine, and yet here we are putting it with the actual engine because we don't really have a separation of engine and editor. So there's a lot of different things you could do to make this better, which I have done in my actual game engine that I'm coding, but we'll leave it as this just so that we can see how it all works. Now, for this picking texture, we're going to need a few different things. We're going to take in a integer. This is going to be the picking texture ID. So this is going to be like the actual texture ID. Then we're going to say private int. This is the frame buffer object. So that's the FBO ID. And then we're going to say int depth texture. And this may not even be necessary, but if you do want to do 3D stuff, this will be necessary. I'll talk about that a bit more once we actually go about creating this. And then we're going to go ahead and say public picking texture, not texture. And we're going to take in an int, a width, and an int, a height. So this is the width and the height you would like to make this picking texture, which will be the same size as your game window. So in my case, that's 3840 by 2160. In your case, it could be 1920 by 1080. It's basically just going to be the same size as your frame buffer. Then we're going to say if not init, width and height. And then we will assert false and say error initializing frame buffer. Well, actually, picking texture. That's a little bit better. And then we'll just go from there. Now, what is this init method? This init method basically just initializes our texture. So we'll take in a width and a height in here. And this will basically create everything that we need. And this should return a Boolean to let us know whether it succeeded in creating the frame buffer object or not. So this is going to be very similar to when we did our actual frame buffer. It's going to look a lot like this. So much, in fact, that I think I'm just going to copy all this and then we'll tweak it to work for this. And once again, another thing we could do to make this better is instead of copying this code, we can make like a factory, which I want to do in the future, that creates frame buffers with different options. And so that would be a better way to do something like this, but we don't have that option right now. Instead of creating an actual texture here too, I'm just going to remove this line. We're not actually going to create a texture. We are just going to create the texture ID ourselves and everything. So we'll go ahead and do this part manually. So right here is where we would usually create the texture to render the data to, as it says there. But what we're going to do is say GL bind texture, and we'll say GL texture 2D. And we're going to say we're going to use the picking texture ID. And then we're going to go ahead and basically do everything that we would do in the texture now, except we're going to add a few more things. You see how we have like the text parameter I and all that stuff? We're basically just going to redo all that in here, except explicitly say everything. So first we're going to say text parameter I, and we're going to say GL texture 2D. GL texture wrap S is GL repeat. So if it wraps in the X direction, we just want it to repeat the texture. And then we'll do the same thing for the T, which is the Y direction. And then I'm going to go ahead and copy that. And we'll say GL texture mag filter. And we're going to say this is GL nearest. So if we are stretching the picture, we want it to choose the nearest pixel. This is important. We want it to pixelate. We don't want it to blur because we're storing IDs in this picture. We're not showing anyone this picture, so we want it to store the most accurate information, not blended information, which is what would happen if we chose the other option for this, which is GL linear, I believe. Okay, and then we'll just do the same thing for the GL texture min filter, and we will also do nearest for that. Then we'll text the image, so we'll upload an empty image to OpenGL so that our GPU has image in store that it can use. So we'll just say GL texture 2D. It's level 0, so it's 0 in terms of MIP map levels. And then we're going to say GL RGB 32F. And so basically we're saying we're storing RGB data of size 32 float. This is important because we're using a float in Java, which is of size 32 bits, which is 4 bytes. So very important that we get all this right. Otherwise, you will get weird errors. And we're going to say we're going to pass in the width and the height. That's how big we want it to be. A 0 border. And that's basically like if you had a border around your image or something. We don't. Then we'll say it's of type RGB. So RGB data is what we're passing in. And we are passing in a GL float. And then we will pass in 0 for the pixels because we don't actually have any pixel data. We just want it to create some empty space so that we can use it. Then we're going to go ahead and say GL frame buffer texture 2D. And we will pass it, not this dot texture to get ID, but we will pass it this dot picking texture ID. So basically, we just created the ID here, and then we went ahead and did everything as it would normally be done. And we never actually did create that. So we should also make sure we initialize this by saying picking texture ID equals glgen textures. and that will make sure that we actually generate a texture ID that we can use. Okay, so this creates a 2D image that we will store on the GPU, and this is where we'll actually write our ID information to. Then we're going to create one more thing. We're going to go down here and say create the texture object for the depth buffer. And once again, I don't actually think this is necessary, but we'll create it just in case. And so basically we're just going to create a depth buffer object so that if one sprite is behind the other, it should get rendered appropriately and we should get the appropriate Z coordinate because of this. So we'll just say depth texture equals glgen textures. And then we will say GL bind texture, GL texture 2D, and we want to bind the depth texture. Then we will say GL text image 2D. So we'll just skip all the parameters. We don't really care about parameters since this is a depth texture. And we'll just pass in GL texture 2D. It's a 0 bitmap level, and we're going to say this is a depth component. And we're going to give it the width and the height. And we're going to say 0 border. We're going to say this is of type GL depth component once again. And the actual type is a GL float and 0 for the pixels because we don't actually have any pixels we're uploading. And then we'll just say GL frame buffer texture 2D once again. And we'll say GL frame buffer. We're attaching a depth attachment this time. And we want to use texture 2D. It's just a 2D texture. And then we give it the depth texture. So we give it the actual ID that it can use. And of course, we have to put in that mandatory 0 for level for no reason. I'll actually go down here and just indent that so you guys can see that. Okay, so we basically just attach the color attachment, which is our actual texture we'll be rendering to our frame buffer. Then we attach a depth texture, which I don't think we did. It's just a depth attachment, so it stores like the Z index of each of our pixels, which may not even matter really, because I think the way we're rendering this doesn't really matter. But better safe than sorry. Now, instead of doing this RBO, we don't really care about a render buffer for this because we just want the frame buffer. So we're going to say disable the reading real quick. That way everything works okay. So for older GPUs. And we'll say GL read buffer is GL none. So basically this says right now we're not reading from any frame buffer. Don't read from a frame buffer. Then we're going to say GL draw buffer is GL attachment 0. Oh, and that's color attachment. Color attachment 0. So that's where we want to draw to, right? So we're saying, okay, now we want you to draw to GL color attachment 0 every time we call draw for this. Then we want to make sure that the frame buffer completed successfully. And then we want to restore, unbind the texture and frame buffer. So then we'll just add in a call to GL bind texture and we'll say GL texture 2D 0. So we'll just unbind the texture and then we unbind the frame buffer as well. That way any subsequent calls won't accidentally get problems. And we'll say return true down here if we make it to the bottom and return false, which really doesn't matter because this assertion will break out of our code for us. But in case you're in like production mode or something, these assertions will be removed. So then you would want it to return before it tried to do anything else. Now we're going to need a few more functions for this picking texture. We're going to make an enable writing, which basically means we're binding the frame buffer. That's literally all this is. And we sort of do it with our actual frame buffer too. And we'll basically just say bind the frame buffer for drawing, and we're going to give it our frame buffer ID. Then we'll say public void disable writing does the opposite of this, which is just copy paste this. And then we just want to bind 0 because we're binding nothing. And that way we don't actually write to this frame buffer. Then we want this last one, read pixel, which takes in an integer x, integer y. Now this is like, give me whatever the pixel at x, y on this texture is. And so we'll say GL bind frame buffer, GL read frame buffer, FBO. So we're saying bind the frame buffer, we're going to read from it. We're not drawing to it, we're reading from it this time. And so that the GPU puts it in a special mode that basically says, hey, we're about to read from this, so get it prepared and everything. Then we'll say GL read buffer, GL color attachment 0. So we're saying we're also reading from the 0th color attachment, which is where you'll remember we're drawing everything to. So we're reading from where we're drawing from, which makes sense because that's where all our texture ID will be stored. Then we'll say float pixels equals new float 3. So we stored RGB data. We're going to read RGB data. And then we'll say GL read pixels X, Y, and we're going to say the height is 1 by 1. So if we actually take a look at these parameters, it says int X, int Y, width and height. So like how many pixels is the width and height, and then the XY is like what pixel location you start from. So we're only reading 1 by 1 area of pixels because we only want to read 1 pixel. Is basically what we're doing here. And then we'll say the format is RGB because that's what we uploaded it as. Then we'll say the type is a floating point number because that's the type of RGB data that we sent. And then we want to give it the pixels so that it knows to put whatever it reads into this float array. Then we can simply return int pixels 0. And this is actually going to give us the wrong result, but we'll see why in a moment. Okay, so that was complicated. Now, how do we go about the rest of this? Well, we still have a few more things to do. Let's go into our window and actually start using this. So I'm going to hit Control N and then just type in window, and we're going to be taken to the window class. Let's go to the top of it. Right below where we have the frame buffer, we'll put in a picking texture. And this is just going to be our picking texture. And once again, I don't like the way this works too. Ideally, you would make this work in a much better way, but we're just trying to get the concept down right now. So we'll go into here and then we'll say this dot picking texture equals a new picking texture, and we'll give it the same size as our frame buffer. So I'm going to give it the exact same size because we want to make sure that we're mimicking our game world exactly. Otherwise, this won't work right, because if these aren't the same sizes, then our IDs are going to be in different locations than what we're seeing visually in our actual frame buffer, right? So we make them the same size. That way we get the same result that we would expect. Then we're going to basically do 2 passes, right? So right here, we basically loop through and we say, okay, let's bind our frame buffer, and then we draw everything to our frame buffer, and then we draw ImGui. So we're sort of doing 2 passes here, but we're not passing over our scene. And in order to do this too, we actually have to update our scene a little bit, because right now, updates our scene and renders it, but we want to split that up into 2 completely separate components because we just want to render. We don't want to do the update. We don't want to accidentally update our logic twice. We just want to render twice. So we'll add a new abstract method in here called abstract void render. Then inside of our level editor scene, we'll go right below where we have the update method, and we'll just make a new method, which is the render method. And so I'm going to delete that, rename this render, and then we'll move this down into the render method. So we'll just say this.current scene, or this.render. And this way we just sort of separate it into 2 phases so that we can control when we're updating and control when we're rendering. Now we'll have to go into level editor scene and override it as well, just so that we get rid of the error messages. So I'll just do that. If you had any other scenes, you would also do it there too. But that should do that. Now we can go back into our window and do 2 explicit rendering passes. First, to make sure we didn't break anything, I'm going to call render here, and we should get the exact same output that we've been getting, and we should get no errors from that texture. Everything looks okay. So I'll go into here, and right before we begin the debug drawing frame, we're going to do our render pass 1, render to picking texture, and then I'll just render pass 2, render actual game. So this is our first render pass. We'll render to the texture, then we will render the actual game, which is of course what's happening. So we'll go up here, we'll say GL disable, GL blend. Once again, we do not want any blending for this. We want to have just pure pixel data. So we're turning off blending, and then we're going to say picking texture.enable writing. Then we're going to say GL viewport 003840 by 2160, or whatever the size you're using for your picking texture is. We want to make sure the viewport so that it draws to the whole texture. This is important too. If you don't do this, then it won't draw to the whole texture. Then we'll say GL clear color 0.0f, 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 0.0f. So zeros all around. And then we'll say GL clear, and we want to clear the color buffer bit, and we also want to clear the depth buffer bit. Although, once again, I don't think the depth buffer bit really matters. Then we're going to have to implement a new function, which I'm going to say is called bind shader on our renderer, and we're going to take in a picking shader. And we'll take a look at why we do this in a minute too. And then we're going to say current scene.render and picking texture.disable writing. And that should be it. Then we just want to make sure we re-enable GL blend. That way, when our actual game goes to use the blending, it can use it again. So we disabled it. We want to make sure we enable it again to restore state as it was. And then we do the second render pass, and that's all good. Now, what the heck is this render bind shader? Well, we want to make sure that we're actually shading correctly. we need to use a custom shader. And so it's a pain the way we're doing it right now to try and change it out, because we're using this render batch method, right? Where each render batch basically just has its own shader. Technically, if we wanted to change this, we would have to basically change this so that every single render batch is duplicated, and that's not good. So to get around this, basically, we know that a render batch will be using one shader, right? So we don't really need to store a reference to that shader in here at all. What we can do instead is store a reference to whatever shader we're currently using inside of here. And so what we'll do is we'll say private static shader, and then we'll just say current shader. And so this will be basically a global object that is like, this is the global state of the game right now. We're using this shader right now. And so then what we can do is we can go down here and just say public void bind shader, shader, and then we'll just say current shader equals shader. So every time this is called, we just bind it to whatever the current shader is. And then inside of here, we'll just basically just say current shader.use. And then we'll have one more method here. We'll just say public static shader get bound shader. And then we'll say return current shader. And then I'm just going to make this static as well, because these should both be static. So this is sort of like our global state setting for our render. This will basically set the global state of the render, and then we end up using whatever shader that is. Now we're going to have errors in here, and that is because now it's like we don't know what this shader is. So instead of doing this, we can just say shader equals render dot get bound shader. And all of our errors magically go away, but really they're not, because if we ran this right now, we would get a completely different type of error, because we never actually set with the error. So I'm going to go up into the window, and literally just up here, this is once again not good technique, but it works. We're going to say default shader equals asset pool dot get shader. And I believe it's assets slash shaders slash default dot GLSL. Let's just double check on that just to be sure. So if we go, yeah, assets shaders default.glsl. And I'm actually going to remove that line too, because we don't really need that. So we've got the default shader, and then I'm going to go here and say shader, picking shader equals asset pool dot get shader, and we'll make that assets slash shaders slash picking shader dot GLSL. And we'll create that in just a moment. But basically this error now goes away. And what we want to do is we use the picking shader from when we're rendering to the picking frame buffer, right? Our first render pass. But then our second render pass, we should switch back to our default shader. And so then if we go into here and we just say render.bind shader, default shader, this should make sure we switch back in time to render the correct data. And if we run our game, well, first of all, we're going to get an error because we don't know what the picking shader is. So I'm going to just switch this to default shader. So basically, it'll just do nothing right now. I mean, it will render to the frame buffer, but we don't really care about that. Oh, and we're going to get an error because we don't have this shader. So let's just comment that out, the picking shader. Now, if we run it, okay, we get everything as we should expect it, which is good. We just wanted to make sure that that's working correctly. Now, let's actually make this picking shader and see what it looks like. So I'll go down to my assets over here, wherever they are. I think they're up here. Okay, they're up actually. So we'll go to assets, shaders, and I'm going to go ahead and say new file and call this my picking shader.glsl. And I'm going to add that to whatever. And then I'm going to copy this, paste it into here, and we're going to have to make a few changes because right now this isn't actually going to work the way we want it to. But if we run it, we should still get the correct result. Everything is fine. We don't get any errors. Now let's change this so that it works correctly. What we're going to do is we're going to say layout location equals 4 and float, or actually vec3 a object a entity ID. And so this is basically the game object ID, which we'll be passing in as a vector 3. And then we'll say out float f entity ID. So then we'll pass it through to our fragment shader so that it gets it. And then we'll just say f entity ID equals a entity ID. And then this should be a vec3, not a float. And then we can go into here and we'll say this takes in a vector 3, which is the f entity ID. So now we got all that right. And then basically we're going to go up here and we'll just say vec4 text color equals vec4 1111. We'll initialize it to 1, and then basically we'll just set it in here to whatever the texture color is. And then right down here, what we're going to say is if the texture color .a is less than 0.5, return, or discard. Otherwise, we're going to say color equals vec3 f entity ID f entity ID f entity ID. What is this doing? This is basically... Oh, and this should be a float. I'm sorry, this should not be a vector3. So our f entity ID, real quick, before we talk about what's happening, just change these all to floats because we only need to pass in one. We don't need to pass them all in. Okay, and then we can change our color output here to be a vec3 instead of vec4 since we're expecting RGB data. Okay, anyways, what does this do? This basically just says if the texture, if first of all, whatever entity we're handling has a texture, so if the texture ID is greater than 0, and if that texture's alpha is greater than or is less than 0.5, which means it's basically invisible, we're just going to discard that fragment. So that means we will get alpha appropriate ID data. So basically, if you have a picture that you attach to an image and it's a donut and it has a hole in the middle, the hole in the middle will get its data discarded, whereas every single other pixel that the donut occupies will take up its entity ID. This is how we get that cool feature where we can click in the middle of the donut and it will still recognize which object we're clicking on. Okay, but that's the picking shader. Let's go back into our window and actually use it now. So we got the picking shader, we just undid it, and then we will go right here, and instead of using the default shader, we'll use the picking shader. Then we'll test and make sure that this is right. So what we'll do is we'll say if mouse listener dot mouse button down GLFW mouse button left. So if we click the left mouse button, we'll just say int x equals int mouse listener dot get screen x, which is a function we don't have yet, and we'll create that in just a function in just a minute. And then we'll say mouse listener dot get screen y, and we basically just want screen coordinates. And then what we'll do is we'll say system.out.print line. What do we want to print? We want to print whether our picking texture or what our picking texture says that particular pixel is. And so we'll say read pixel xy. Okay, so we'll just print out what is the pixel's actual color there. Now let's implement these very quickly. We'll just go into the mouse listener, control click if you don't know how to do that. And then we'll go down to where we have a get ortho x because we'll just modify this a little bit to get the screen x. And this will be the screen according to the game viewport. So these will return coordinates as if it was like this top left of the game viewport is x and the bottom left of the game viewport is y. So I'm just going to copy these very quickly. And I'm not going to explain too much about how this works. We're basically doing almost exactly the same thing as we've done before, except what I'm going to say is once we do the current x times 2 minus 1, we basically just want to ensure that we get that back to a range of 0 to the screen's width. And we can do that very simply just by removing all of this. We'll just remove all of that. And then instead of multiplying by 2, subtracting by 1, what we'll do is we'll just multiply by 3840 or whatever your screen width is. These are horrible. They should not be hard-coded like this, but we're doing it for now. And then for this one, what we'll do instead of this is we'll just say times 2160. And because this is flipped, we need to do 2160.0f minus whatever this value is, and then we should be good. And then we'll just return that y. Those should give us the appropriate screen coordinates. Once again, I didn't go over that too much, but it's very similar to this. Look at the code for a little bit, and you should be able to get what's happening there. Now, if we go back into our window, let's check it out, see what happens. So if we run this, and if I minimize it, I'll click on this object. It's kind of hard to see. Okay, so it says 0 when I click it. It also says 0 there, 0, 0. Why is it saying 0? Because we're not uploading any data. I just realized that. So let's go to the render batch. Let's go here. We need to add another vertex attribute. So first we're going to say vertex size is now 10. Private final int obj ID, or we'll call this entity ID offset equals, and before we do that too, actually we should say private final int entity ID size equals 1. And then down here we'll say the offset is just text ID offset plus text ID size times float.bytes, and that should give us the appropriate offset and size. So then we'll go down here, we need to enable one more attribute. And the reason we're doing this, remember, is because inside of our picking shader, we say we have the entity ID coming in location 4, but right now we don't have location 4 enabled. We just have up to 3. So we'll say vertex attrib pointer 4, and then we're going to say that's the entity ID size, and that is type float, and it's not normalized, and we'll say vertex size byte, and then we'll say entity ID offset, and then that should be good. Then we'll just say GL enable vertex attrib array 4. Now that's not all we have to do. The data is not going to get uploaded magically. We have to actually upload the data. So in order to do that, we'll just go down here, and right after we load the texture ID, we'll say load entity ID. And that's simply offset plus 9. We're just going the next vertex, the next float, and then we'll just say that is the sprite.gameObject.get UID, which, if you'll remember, is the game object's unique identifier. So that's exactly what we want. Now let's run it and see what we get. All right, so if we close that and then we click on an object, 14. Awesome, 3. 20. Now, I don't know if these are actually correct, but they sure seem correct to me. And that's really cool. We're clicking on an object and it's showing the correct object. Now, let's do something a little bit more interesting. If I drop this guy in, and you may be able to see if I click just barely onto his pixel, we get 31. But if I click off, we get 0. Now, we don't want it to return 0 if it doesn't hit an object. We want it to return -1. And so in order to do that, it's very simple. What we'll do is, and why is it doing 0 too, real quick, before we actually do this? Why is it 0 if I don't click on an object? And that's because we're looking at this color. So if I make this 1, we're looking at the red color, and we change the clear color to 1. Then if I click onto the background, we get 1. If I change this to 0.5, we would get 0.5. We get whatever this red color is, and that's because we're just using this red color right now. And so in order to fix that, what we're going to do is we're just going to go into the render batch one more time. We're going to upload the ID +1, just because we're going to use 0 as a flag that this is an invalid object, and then we'll go back into our picking texture, and we will return integer pixels 0, and we will subtract 1. That way we get back to the appropriate ID. Now if we go in and we click the background, we get -1. But if we click an object, we get the object ID. Okay, I'm not going to go any further today because this is way long, and you guys are probably itching to be done with this tutorial. But we have just implemented a picking texture, and we've just implemented picking, pixel perfect picking. So our game engine, we can now click on objects and know which object we're clicking. We know the object ID. This is great because now we can click on it and we can show its properties in the properties panel. This is amazing, guys. We are one step closer to a real kind of working game engine, okay? In this episode, what we're going to be doing is fairly quick and simple, but it needs to be done. We're going to be cleaning up a little bit of code, but we're also going to be enabling the picking. So I'll actually show you real quick too what I've got done. We're going to be basically making it so that you can click on an object and it pulls up its properties panel over here, and then you can just change the color right now because that's all we've got, which is still pretty cool though, because you can now go and change the color of any object and you can click on them. The next logical step would be to create a gizmo system where you got the arrows and stuff and then you can move them around, which will be our next step. But for this episode, we're just going to be getting this done because it's pretty simple and it's pretty quick. There's going to be no explanation on what we're doing really, visual explanation, because it's pretty straightforward. All right, without further ado though, let's just get started. So to do this, we are going to first reorganize a little bit of our code because I don't like the way that some of this is turning out. So first of all, inside of our ImGui layer, we have this game view window that we're using, right? And the game view window is currently completely static. I don't like that. It's basically the same thing as a global when you have a completely static class. So what we're going to do is remove the static keyword from all of these functions because that's the way it should be. When we do that, we're going to get an error though. And that error is just going to basically say, hey, we're using this in ImGui layer. We need to be able to have like an actual instance. So we'll change this to lowercase g, and then we'll go down here because we're using it over here as well. We'll change that to lowercase g as well. And then we'll just provide an instance to the ImGui layer. So I'm going to go up to our variable declarations and just say private game view window, and then that's just going to be game view window. Then we're just going to shirk our responsibility and pass it to somebody else and say supply us with a game view window. And then we'll just say this Object.GameViewWindow equals GameViewWindow. Actually, do we even need to do that? No, we really don't need to do that. So let's remove that. We can just say this is just a new GameViewWindow because it's a parameterless constructor. So it doesn't really matter. We'll just create that dependency directly in there. And then you'll see we get compile with no problem and everything works the same as it was just a second ago. Next, we're going to go into here and we're going to create a new class and call this properties window. And this is going to be the properties window in our actual game scene. So right now the properties window is just this thing right here. It's called inspector. So maybe we'll change this to represent properties instead. But basically we'll just get that working a little bit better. Right now what's happening is we have this thing in our scene. So if we go to our scene class, we've created a function called scene ImGui, which then calls regular ImGui, which just isn't desirable. And this wasn't a very good way of doing this in the first place. Reason being, why the heck does the scene have the active game object? The scene doesn't need to know about the active game object, right? The scene doesn't care about whatever the active game object in the editor is. What cares about that is the properties window right now. That's the only thing that cares about it. So a better place to have this would be inside the properties window. So we're going to copy this and we're just going to paste that into our properties window. And then we're going to create a function. We're just going to call this public void ImGui. And this will basically be our ImGui function. We'll go back into the scene and we will strip all of this out. And then we're just going to completely remove that function because it should not be there in the first place. This is much better. Now we'll go back into our properties window. And then inside here, we'll just paste that code that we just took. So that basically now the properties window is the one in charge of this. And we're going to add another function here. Just call it update, take in delta time, and we'll take in a scene. And we'll call that current scene. And this will basically just be in charge of when the user clicks the mouse, then it'll update whatever the active game object is, because this properties window is the only thing that cares about the active game object. We will have a gizmo system that also cares about it, and we'll update accordingly whenever that happens. Now, we have an error in ImGui layer because of this refactoring. So you can see the errors over here too, the little red lines. So we'll go into here. This is now expecting the parameters. So or actually, no, this is now gone. We just took this function out. So just change that to ImGui. And then over here, we're going to say properties window .ImGui. And we are also going to say properties window .update DT and current scene. Now let's actually go and create this properties window object. So we'll go back up to the top, add another object up here, call this properties window, and just paste that. Then we will go ahead and say this .properties window equals a new properties window. Now that logic has been offloaded and is now in the properties window and the scene doesn't care about it. Let's try and build this. We may, we're going to get an error because we referenced the active game object in here, which was never a good fit anyway. So we'll just delete that code. This was inside of level editor scene too, right up here. And so we'll just remove that code because we don't need it anyways, because now, there we go. And we don't get a properties window anymore, which is to be expected. That's fine. We'll fix that in just a second. Now, how do we get that properties window in there? Well, I kind of alluded to it. We'll be doing it inside of this update method. And this is where the new stuff is going to sort of go in, but even then, it's really not that bad. So if we go into our window, we can literally pull out some code that we did in here. Remember, we were demonstrating to see if our picking works. So we did this whole if, and then we just print out whatever pixel or the ID that we clicked on. I'm going to copy that. And then I'm going to go into the properties window, paste it into our update method, and just hit OK to import those things. Now it's going to say, OK, I need a picking texture. Now this we will, and I'm also going to change this to private because no reason for that to be protected. We'll need a reference to the picking texture that is being used inside of the window. So we'll just say picking texture, and then we'll make a constructor and we'll just say properties window, and this takes in a picking texture. Now, so this is going to have a cascading effect where we're going to have to update a couple more classes to represent this. So now ImGui layer is going to give us an error because it says, hey, we need that picking texture in here. So we'll just go ahead and say, we'll take this into our constructor as well. And then we will go ahead and just pass that along. Then we'll go up one more into the window because the window is creating the ImGui layer. And now we can finally pass in this picking texture that we have here. So if we just copy these and move them below this creation, then we can go ahead and pass in that picking texture. There we go. This is nice. This is much better than creating static functions, which are just global functions. This gives us a nice clear chain of dependencies, right? The window has ImGui layer dependent on it. It also has a picking texture that it is dependent on, which is because the properties window depends on that picking texture. So nice clear chain. We know exactly what's happening. Now, what are we going to do? We're going to say, well, the active game object equals, and then we'll just say current scene dot get game object. And we're going to create this function in a second. So what this function is going to do is it's literally just going to say, okay, you give me an ID, which remember, this is what the read pixel function returns. It's an ID of a game object. You give me an ID and I'll return you a game object. Or null, which is good. If it's an invalid ID, it'll return null. So let's go into our scene and see how to create that real quick. We'll just go right below where we have add game object to scene. And we'll simply say public void, or actually public game object, get game object. This takes in an ID, which is the game object ID. And then we'll go ahead and we will just use a fancy lambda expression that Java gives us to find something in a list real quick. So we can get this thing called an optional, which is basically just like null or a game object if it is a game object. And then we'll just say result equals this dot game objects. So this is a list dot stream. And then we'll use some Java 8 features here, which will basically just use a lambda to make this stuff a little bit easier. So we'll say dot filter, and then we'll say game object, where the game object dot get UID equals the game object ID that was passed in. So what this does is this says, hey, filter this list, game objects list, to every game object where the game object's UID equals the object ID that was passed in. This should only return us one game object. So then we'll say dot find first, which just gives us the first result. Then we'll just say return result dot or else null. So basically this just says return the result if the result exists. If it doesn't, then or else we'll just return null, which is basically what we'd want to do. If we didn't, then it's going to give us an error because right now that's just optional. So we just have to add in this clause just to make sure we're making it explicit that we are okay with returning null. Now I believe we should be good. Properties window, the error goes away and we're all fine. And let's make this a little bit more explicit too. We'll say int game object ID equals, and then we'll do that. Then we'll say active game object equals current scene dot get game object ID. There we go. Now it's very explicit what's going on here. Okay, let's run this and see if it all works as it should. So if we click on an object, we get an inspector. And if we change the color, it's change the color of that object. We click up here and we're changing the color. Cool. This is awesome, guys. And this is pixel perfect. If I click outside of here, notice how the inspector window disappeared because I didn't click onto an object. If I click just below this cloud, it doesn't see it. If I click over in this blank space, it doesn't see it. And that's because of the picking that we enabled. So this really highlights how powerful that feature that we just did was. I mean, this is great. Now we have pixel perfect picking. Doesn't matter your zoom level because it's going based on the pixel you're clicking. This is amazing. And we have an inspector window that pops up for us now. Very cool. Let's go ahead and change the name from inspector to properties just because this is our properties window. There we go. And that should be about it for this one, right? Yep. I'll put it down here. All right. So another very quick episode. Sorry I didn't do a physics episode this week. Once again, I did not prepare. I need to prepare for those because otherwise they'll be very bad. I hope you guys enjoyed this. If you did, please hit like and subscribe. And I think I'm going to have 600 subscribers by the time this video releases. So thank you for that. That's awesome. Let's see if we can get 1,000 by the end of the year. That'd be super cool. And our game engine is really starting to come together, guys. We're going to implement gizmos next week, which will be another really cool feature because then we can move these things along the gizmos, you know, click on the gizmos and everything, and we can hopefully rotate them. Another thing that the game engine really needs is some camera movement. Right now, the camera's in a fixed position. We can't really move it around or anything. So that's another to-do item that will probably come right after we do the gizmo implementation. So in the last episode, what we did was we got picking working correctly, so now you can go around and click on any object and it will switch to whichever object you clicked on and then bring up its properties in the properties panel. This is great, but we need a way so that we can actually start building levels. So in this episode, we will be implementing a camera, and this camera will also support smooth movements, and it will also support recentering back to the origin of your scene just in case you get lost. So if you go somewhere way out here and your zoom is way messed up, you can always just go back to the center of your scene, or eventually when we have a properties panel over here showing all the game objects, you can click on one of those and center on the game object, which will also be really cool. But by far, the most exciting thing is this smooth movement. So we'll take a look at how all this works in this episode. So let's get started. Before we get started, as always, we are going to look at how this will work in theory, and then we will actually code this. So how do we get the camera to move in the opposite direction to which we drag our mouse? And how do we get it to do that smoothly? Now, this is actually a little bit difficult to get the first try. I always have to mess around and setting the settings properly, like sensitivity and everything. That is by far the hardest part. But let's say that the user clicks here, and this is where they start the drag. So this is the original click position. Then they drag their mouse this way. Now in my mind, when somebody drags the mouse this way, they want to move the camera this way. You can set it up differently if you would like, but this is how we will be doing it for this tutorial. So they click the mouse, they drag it this way. Now, how do we know what distance to move the camera? What we want to do is we want to figure out what the distance between these 2 points are. Then we want to move the camera so that it moves in a proportional distance this way, because we would expect it to move proportionally to how we moved the mouse. So what we need is we need the original mouse position, and then we need this position, which is the position, and this would be in the next frame too. So this is all happening within a frame. So I'm exaggerating the distances. The distances in actuality are going to be very, very small, but that is in essence what's happening each frame. So we get that new position. And now this is literally just simple vector addition, subtraction, right? So if we have this and we have this point, then getting the distance between those 2 points is literally as simple as saying this minus this. So to get that distance, we'll just call that delta. It's just equal to pose minus original. All right, so now we have that distance, but we don't want to just jump the camera from here to here immediately. I mean, you could if it's a frame, but if you get a big lag spike or something, it's going to glitch and then it's going to seem like it's jumping. So it just won't look that good. So instead what we'll do is we will interpolate this. So linear interpolation, also known as LERP, is literally just saying if you have some start and some end value, so that's your start and that's your end, and you have some delta time that you want to apply this over, so some time variable, then you can interpolate this so that it gets applied evenly across the time. So in our case, delta time would be our time variable, right? The time between the last frame. Our start would be this original position. Our end would be this position that we want to get to. And so what we do is we say, okay, just multiply. So we'll add part of this distance times whatever time we currently have. So delta time may be here. And so when we multiply delta time, we will end up here. And then what we'll say is we'll say add this distance, which will get us to somewhere like right there. And then we do this again the next frame. And then we move original to this new position. So then we say, okay, now original equals this. So that the next time we do it, we'll move right here, and then it will smoothly move across until we get to the next point. However, there's one extra thing that you want to think about, and that is for the other scenario I showed you where the camera's like way over here, but you want to move it all the way back to the center. And so to get it to move smoothly and then speed up as it gets to the end so that we don't get this weird situation, because if you keep doing this, you'll notice that what ends up happening is it actually, as you get closer to it, it never fully reaches it. And so you just get slower and slower and slower, and then you get this problem. And I'll show you that too once we actually start coding this. But to avoid that, what you can do is you can increase delta time for each time step you take. So we can say, okay, so for each frame that we move, we'll actually increase the steps delta time is taking. That way we get to the end quicker. So you would just say something like delta time equals 0.1 plus equals 0.1 times delta time. And so what this does is basically for every time step that we take, we're adding on a little bit extra bit of time so that the next step we're taking is bigger, which means we will get closer to E faster. Okay, that may make sense, that may not make sense. One last thing that we're going to talk about is zooming. So if you're zooming out and you're zooming in, it can be hard to make it zoom out and zoom in a speedy way. And what I mean by that is if you're taking the same step of zooming out each time, you're going to actually have to take a larger step, because when you zoom out once, and say you zoom out by a portion of like 0.1, that's going to zoom you out a pretty good distance. But then if you're already zoomed out to like a 10x zoom level, so you're way out, and then you just go 0.1, that's going to be a relatively small step. And so you're going to have to scroll a ton just to get it to keep zooming out. And so one way to combat this is to zoom out faster the farther out you get. Well, how do you make something go faster the farther out? And we can use, once again, just mathematics and use a exponential function, right? Because an exponential function looks like this. So when you get really close, it starts going slower, 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 slower. When you get really far, it gets bigger, 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 bigger. And so if we use this exponential function to curve our zoom level, then as our zoom level is at 10x, and we say, okay, now we want to go 0.1. Well, 0.1's here. Well, actually, that's a pretty big gap. Whereas if we're here, which is like 1, and we take 0.1, the rise is relatively small. So even though we're taking the same step, we'll actually be taking bigger y steps each time. So we'll use an exponential function to ensure that we get a nice, fast, and even zoom. And I'll let you know the settings I used, just so that you guys can get some good settings with yours. All right, let's take a look at the code. I am back in our project here, and as you can see, this is the same place we left off. You can click on the objects and change them, and it just switches to whatever object you click on, which shows us that our picking is working. So first step, let's go and add a new component, and we're going to call this our editor camera. And the reason I'm calling it editor camera is because this is going to be different than a regular camera component. And so we're going to want to make sure that is clear for like game cameras. And we'll have game cameras pretty soon too, because I think that'd be pretty cool to do. It's going to require a bit of work, but it'll definitely be a cool thing. So how does an editor camera work? Well, first of all, we need to make sure that we extend component, because we are just going to be using this as a component, easiest way to get it into our sort of system. So then we'll just say public void update will override that method so that we can use this. And we will create a constructor for our editor camera. And we're going to say that this constructor actually takes in a camera, and this is going to be the level editor camera. So just nice to pass it in, and then I'm going to hit Alt Enter, and then create field for parameter, then just hit OK. And there we go. So that created that real quick. And then we're going to need that other variable I mentioned too, private vector to f click origin. So where did they click on when they initially clicked? So we'll say this.click origin equals a new vector to f. And then inside of our update method, we will have to do quite a few things. So first of all, we have to detect if we are dragging the mouse or not. And normally I would say we could just use the mouse listener's is dragging method, but it's not working properly, and I haven't looked into fixing it yet. So we will fix this in a future tutorial, and then we will switch this up to use that. Instead, what we'll do is we'll just use a simple debounce. So what we'll say is private float drag debounce, and we'll set this to a small number like 0.1. So this means after 0.1 seconds, the drag will initiate. So it'll be like, oh, we're dragging, which is usually fine. Nobody will notice that 0.1 second delay. So then we'll say if mouse listener dot is dot mouse button down, and then we'll say GLFW mouse button middle. You can change this, of course, to whatever you like. I just think that the mouse button middle is good. And then just make sure to import that. And we will say drag debounce is greater than 0. Then we'll say this.click origin equals new vector to f, and we'll say mouse listener dot get ortho x, mouse listener dot get ortho y. So we get the mouse position in world coordinates because we want to make sure that we are doing everything in world coordinates. That way we get an appropriate like movement distance according to what the user would expect when they're looking at it. So then we'll say drag dbounce minus equals dt, and then we will just return. So this way we just get a click origin that is appropriate, and then we will make sure to decrement dt until we're outside of this dbounce. And let's actually make this dbounce 2 frames. So if we're running at 60 FPS, that means we're running at 16 milliseconds. So that would be 0.016 seconds. So then we'll just say 0.032, which should be 2 frames. So if they are holding it down for 2 frames, we'll assume it's a drag. Then we'll say else if mouse listener dot mouse button down GLFW mouse button middle. We can assume that the drag dbounce is now less than 0 because otherwise we would have entered this one. So if we're in here, then we'll say vector 2f mouse distance or delta. I'll call this delta because that's why I called it in our drawing, is a new vector 2f. Once again, mouse listener to get ortho x and mouse listener dot get ortho y. Then we want to make sure to subtract, I'll move this to a new line, dot sub, the original click pose. So click origin. Okay, and all this is going to do is it's going to get that delta value that we talked about, the delta value between when we first clicked and where we are in the next frame. Then we will simply say level editor camera dot position dot sub delta dot multiply by dt, and we'll need something else there too, but for now this will be fine. And then like I said, we're going to lerp the original click position, so that way we get like a smooth movement. So then we'll say this dot click origin dot lerp new vector 2f, and we want to get where the mouse is right now. So that would be mouse listener. Well, let's actually just cache that as another variable, make that a little bit easier. So we'll say vector 2f mouse pose equals new vector 2f, and then we'll say mouse listener dot get ortho x and mouse listener dot get ortho y. Then we can just switch this to use mouse pose, move this back up, and then we can just say mouse pose, and we want to lerp it by delta time. So this sort of gives us that smooth movement. It'll just reset the click origin, then lerp it, and then we will continue dragging and continue lerping. So that's more of a smooth movement. It's not very jerky if you're sporadically moving the mouse. Now you could do this other ways. This was just the best way that I found, and it sort of made it work the best for me. So now if we go back into our scene and we click our mouse button, nothing happens. Surprise, surprise. That's because we have to go into our level editor scene first and actually add this component. So we'll just go up to level editor stuff, and we'll say add a new component, editor camera, this dot camera, and we have to make sure that the camera is created. I did not when I first did this, and that messed it up. So let's move this up to the top so that we actually have a camera to pass into our editor camera. Now if we run this, okay, so if we move the mouse, first of all, it's like moving the wrong way, but you'll notice it's smooth movement, and it's definitely like a smoothing of whatever the mouse is doing, but it's not going the way I want it to. And so we can fix that pretty easily. Okay, and so the only reason that that was not working correctly is because the sensitivity was very low. So if you just add in a variable called drag sensitivity, I set it to 30, and then as long as you mark it up here, we multiply the delta times dt times the drag sensitivity. Now, when we go back in, you'll notice that this moves pretty much directly in response to wherever the mouse is going. And it's kind of jerky, and that's because we never reset our dbounce. So we just want to make sure that we reset the dbounce too. So we'll say if drag dbounce is less than or equal to 0.0f and not mouse listener dot mouse button down GLFW mouse button middle. So if the middle mouse button is not down and our drag dbounce is less than 0, then the dragging has stopped. So then we can say drag dbounce equals 0.1f, reset that, and we should be good. So now if we go back in, we should get rid of some of that jerkiness for when we restart a drag. Yep, and sure enough, now you can click and drag, and it all works pretty good. All right, cool. So now we have dragging done. Now we want to make sure that we get zoom done. So let's add in the zoom factor. And like I said, in order to get that to work, we will just use a exponential function to make sure that it zooms appropriately. So let's say if mouse listener dot get scroll y does not equal 0.0f, So if they are actually scrolling, then we'll say float add value equals float math.power. So this is the same as an exponential, and we will use the base as the scroll. So we'll say math.absolute value of mouse listener dot get scroll y. So that will be sort of our base. And then we want to raise it to the power of 1 over the level editor camera.get zoom, which we do not have yet. So let's move this to a new line first of all. And then let's actually create a zoom level for our camera. So if we go into the camera object, then we will add in another variable up here. We'll just call this private float zoom equals 1. So 1 is like your 1-to-1 ratio. So this is no zoom. And then so on and so forth as you go up and down. And actually, let's just go up to here. Say Alt-Enter, create getter and setter. And then we will also go down here and say public void add zoom, and then float value. Then we'll just say this.zoom plus equals value. So we have all these functions that we can use, but it's not actually going to zoom anything out right now. And so the way we get it to actually zoom is we just modify the projection according to the zoom. So we'll say just multiply the projection size by the zoom, and that will make sure that we actually zoom out and zoom in as you would expect. Okay. So then if we go back into here, this should be good now. We do 1 over the camera editor.getZoom because that makes sure we have an exponential function that works inversely proportional to the camera's actual zoom level. And then we can say add value times equals math.signNum of mouse listener.get scroll y. And what this does is this basically says if they're zooming out, make sure you get the sign, which is a negative, and then zoom out. And then if they're zooming in, make sure you get the sign of that. And we should actually make this a negative so that it zooms the correct direction. And then we'll just say level editor camera to add zoom and our add value. So if we do this now and we zoom, nothing happens. Why does nothing happen? That's because we have to go into the ImGui layer and make sure that it knows that we want to pass in the zoom as well. So we have this GLFW set scroll back right here. And inside here, we're just going to say mouse listener dot scroll callback. And then we will pass in W, X offset, Y offset. So we'll just pass everything in. We may modify this in the future because this will actually zoom regardless of where the mouse is. So, nope, the zoom still isn't doing anything. So we have to figure out what's going on with that real quick. Okay, and so the reason that it's not actually zooming is because I forgot to actually adjust the projection matrix. So if we go back into camera, you'll notice that we actually have to call this function in order to apply that new zoom, which is never being called. And so the easiest way to get this to work is just to go into level editor scene, and then we'll just say this.camera.adjust projection, which should adjust the projection. So now if we go into here, we zoom out, we zoom in, you'll notice it goes, but it never stops. And that is because we have to go into our window, and then right at the end of the frame, we just have to make sure that we call mouse listener.end frame. So we go into here one more time, and if we do this, there we go. So you'll notice we're zooming, it's just taking very big steps, which is not good, and the grid is messed up, which we will also have to fix. So in order to get it to take even steps, we just need to add a sensitivity to this. So we just want to make sure that we add a sensitivity here. So we'll say multiply it by scroll sensitivity, which will just basically make sure that we can control how fast that we are zooming. So I'll just go ahead and add this right below our drag sensitivity. So we'll say private float scroll sensitivity, and I think I set this to 0.1. Yes, so 0.1. Let's run this one more time, see what happens. Okay, so now the zoom is working better, and you'll notice it slows down as we go farther in, and it speeds up as we get farther out, which is nice. And if we move around, it moves around, except our grid lines are messed up. So let's fix those up real quick. It's relatively simple. We can look into here and notice immediately that we're just not taking into account the camera zoom in the projection size. So what we can do is we can just say camera equals window.getScene.camera. And then we will just replace all this stuff too with camera because there's no reason to have them calling the functions. Okay, and then we can go into here, and as long as we multiply this by camera.getZoom that should fix the problem we were seeing. And then camera.getZoom, just to make sure we get the appropriate amount of vertical and horizontal lines. So if we go into here one more time, zoom out, almost working. We just have to make sure to also put it inside of here as well. So then we'll say camera.getZoom, and then we will multiply this guy by camera.getZoom as well. And run this one more time. Now we should be good. Okay, there we go. So now you'll notice that the grid expands as we expand the zoom, and we get all this. But now what happens if you're like way out here, then you zoom in, then you move around a little bit more, you're lost, right? And you don't really know. Well, we know it's right here, but what if you do get lost for real? How do you get back to the center? And we're gonna add in a hotkey so that it just moves the camera back to the center in the original zoom, which is nice to have just in case you ever get lost in your scene. And so we can add that by just going back into editor camera, and we will just add in a reset value. So let's go up to here and we'll say private boolean reset equals false. And so if reset is set, then we want to reset the scene. So then we'll just say if key listener dot is key pressed, and then I'm going to say GLFW key keypad decimal, which is the same hotkey in Blender that is used to center on an object. So that's just the decimal key on your keypad. You could set it to whatever key you want. And I'm just going to say reset equals true. Then we'll go down here and we'll say if reset. The reason we do it this way too is because this will happen over multiple frames. And so we just want to make sure that we have a flag instead. Then we will smoothly move the camera by using the lerp function once again. So we will linear interpolate. So we'll say level editor camera dot position dot lerp, and we want to lerp to 0, 0, which is just the place we want to go. And I would say DT, but we'll see why this will not actually work very well in a minute. And then down here, we're just basically going to say if it gets relatively close, then clamp it. So if math.absolute value of level editor camera dot position dot x is less than or equal to 5, and the reason I chose 5 is just because that's what worked best. Level editor camera dot position dot y is less than or equal to 5. And I'll move this to a new line. And we will do the zoom in just a minute. So we'll just focus on position for now. So we'll actually leave off that final and. So then if it's pretty close, then we'll just say level editor camera dot position dot set 0, 0. That way we were there exactly. And then we'll just say reset equals false. So we just sort of clamp it there if we get close enough. Now let's run this and see what happens, because there's a problem with this. And it's the problem I mentioned before. So if I hit dot, you'll notice it moves. And it just keeps moving. It's still moving. It's still moving. So it sort of just very slowly settles in, and we don't want that. So the way we can fix this, I looked up on Unity's website to see how they fix it, and we'll use the same method, which is basically that whole adding a fraction of dt to our increment so that it speeds up as it gets closer. So we'll say private float lerp time, which is just sort of our flag, and we initialize that to 0. And then down here, we will say lerp using lerp time. And then after we lerp, then we will say this dot lerp time plus equals 0.1f times dt. So we just sort of add a portion of dt to the lerp time so that it gets bigger every time. That increment gets better. Then when we reset it, we'll just say this dot lerp time equals 0. Now if we do this and run it one more time, you'll notice that it just sort of clamps into, it goes faster and then it clamps into place way quicker, which is nice. So this is good, much better. The one thing we don't have though is the zoom. So if we move, it moves us back to the center, but we would like it to move the zoom as well. So we'll just manually, there is no lerp function for a float, so we'll just manually lerp it ourselves. And the way we can do that is we can just say level editor camera dot set zoom, and then we want to just sort of add. Actually, let's just click into here and you can take a look. They just say plus equals other x minus this x times t, which is your delta time. So we'll do the same thing. We'll just say plus equals 1, which is the value we want it to go to, minus the current zoom times t. So we'll go into here and we'll say we're going to set the zoom to the level editor camera dot get zoom plus, and then I'm going to move this to a new line, 1.0f, and let's actually do this minus, level editor camera dot get zoom. So 1 minus other x times lerp time. So we do plus equals 1, which is other x minus this x times delta time. Cool. And that should do that automatically for us. And then we'll just add in the zoom. Actually, we'll not even add the zoom check into here. We'll just say this dot level editor camera dot set zoom to 1. So once we clamp, we get to the right position, we'll just make sure to clamp the zoom as well. And so if we go down here, we zoom out, then you'll notice it all works perfectly. Cool. So if you hit your hotkey, which mine is numpad 0, but if you have something else and you're like way zoomed in and you just want to get back to the center, you can just hit that hotkey and it'll take you there with everything sorted out perfectly. All right, so that is it for this tutorial. I hope you guys enjoyed it. You'll notice that this does hit a limit. So if you zoom out too far, it doesn't work quite so good. And we can fix that in a future date. You can literally just hit a zoom max level so that you can zoom out. Also, I want you guys to help me solve this. So if I click an object, the farther away I get from the origin, you'll notice the more that this object is not lined up with the mouse. And then once I get back close to the origin, it's lined up. I'm not sure why it's doing that. I haven't had time to look into this, but if you guys want to look into this and let me know if you find out why that is and how we can fix it, that would be awesome. So leave a comment below telling me how to fix this if you find it out. So in the last episode, what we did was we built a camera movement system so that we can now pan around our scene and then reset our camera. In this episode, we're going to be setting up the basis for our gizmo system. So when you click on an object, it will pop up the gizmos that you will use to translate and rotate and whatever with them. Now, currently, it's not actually working. We're just setting up this process first. And we will also be adding in a rotate function because I realized we don't even have a way to rotate sprites. And we really need a way to rotate sprites because that's a pretty important part of building games. So we will be building this little gizmo, the basis of it, and then we will go into depth on how to make it actually work in the next episode. Before we start talking about how this works, I do want to thank you all because I forgot to in the last episode for 700 subscribers. We are really close to 1,000 subscribers, and it would be really cool if we got there by the end of the year. So thank you so much for that. Now, let's go on with the tutorial and see how this gizmo system will work. So the gizmo system is pretty simple in essence. What we're going to be doing is basically creating some sort of system where when an active game object is selected, so when the user clicks on some game object, we basically just move two dummy game objects over here, which are the arrows. So the arrows just are another game object with a sprite. So basically these two things are game objects themselves, and we just store them inside of a class called a translate gizmo. And literally what we do is we just say if there is no active game object, then set the opacity to 0. So we just hide them. And then if there is an active game object, then turn the opacity back up to 1. Now this is mostly simple, but there's a couple other things we have to do to get this working fully the way the engine works right now. And one of those things is rotation, because for some reason I never implemented rotation for our sprite batching. So in order to rotate a sprite, it's not that hard. If you have a sprite that looks like this, but you want to rotate it like this, currently what we do inside of our batch system is we add each vertex to the batch. And so normally if you had rotation or something, you could do that on the GPU using a transformation matrix. But since we're batching, we have to do this on the CPU side with our transformation matrix. So we basically check and see if the rotation is not 0. So if it's something like 45 degrees, we construct a transformation matrix using the translation, rotation, and scale. And we want to make sure that we are rotating about the z-axis. So we just want to make sure we're rotating about this axis since we are working in 2D. Then when we create this matrix, we can literally just multiply this matrix by these points. So if we multiply this matrix by each of these points, in this case it would just be like some vertex, then this will transform the vertex to the appropriate position. We're sort of doing this manually, but we'll just explicitly do it for rotation matrices. The reason that we don't use a matrix when we're building the regular one is because it's a little bit more expensive to do matrix multiplication than it is just to do one regular multiplication, which we can do. And I'll show you more of what that means when we actually get into the code and look at that. Now, I will also admit that the system we're going to be using for this is not the greatest, and that's because we don't have an event system right now. That will be like the next step because we need a general event system to be able to pass events around our game engine, because right now it's really hard to tell somebody what the active game object who wants to know without creating some ridiculous chain of dependencies, which is what we're going to be doing in this episode. All right, but with that brief intro, let's actually go into it and just sort of create this translate gizmo class, which will hold a couple of game objects, which are actually going to be the arrows, and then we'll just sort of set the transforms to the active game object. Okay, let's check this out. All right, just to reiterate, where we left off was we just have this camera, which we can move around, zoom out, zoom in, and recenter using a hotkey of your choice. And we have picking enabled. So using the picking, we will be able to implement this gizmo system to sort of place the gizmos on the active game object. Okay, so let's go ahead and create a new class inside of our components, and we will call this our translate gizmo. So the translate gizmo will just extend component because we just want another component, and we'll have a few different variables in here. We're going to have a lot of variables in here. So we'll have a vector 4f for the colors. We'll say this is the x-axis color, and I'm going to create a new vector 4f, and we're just going to color this red. And then we'll have vector 4f x-axis color hover, which we don't actually use yet, so I'm just going to leave that uninitialized, and we'll tweak it when we get around to it. And then we'll also have a vector 4f y-axis color equals a new vector 4f. This one will be blue. And we will have a vector 4f y-axis color hover, and this will just be a new vector 4f. And let's just copy that and paste it so that I get rid of that typo. Okay. So then we're going to need a couple more. Like I said, we want to actually create game objects and sort of move these game objects around, and these game objects will store it. I wouldn't do this normally. It's just not ideal. But the way we have our render batch working right now, we can only really add images, which is what those arrows are for the gizmos. We can only add them by using sprite renders that are attached to game objects. Because when we load the sprite render, we automatically assume that once we get into here, that sprite render will be attached to a game object. So there's no really a way to beat around this bush unless we go and do some extensive refactoring of the render batch, which we may do in a future tutorial, because that's what I did on my actual game engine that I'm working on the side. But for now, we'll do it this way, and this way works. So we'll just do it this way. So let's create a game object, and we will call this the x-axis object. So this is going to be the object holding the x-axis little gizmo arrow. And then we'll create another game object, and this is the y-axis object. Once again, just holding the little arrow. We're also going to get a hold of their sprite renders. So we'll call this x-axis sprite, and we will also get the y sprite. So y-axis sprite. And then we will store a reference to an active game object. So we'll say active game object, and this is what we will use to determine where to place those objects. And it's just going to be null initially because we don't know what it is. Okay, and then finally, we're going to need a reference to the properties window. We'll wait on that though, and we'll see why we need that in a minute. Okay, so anyways, let's go ahead and say public translate gizmo, and this will take in a sprite, and we'll just call that the arrow sprite. And so the arrow sprite actually looks like a very simple sprite. Let me pull it up real quick. All right, so this is the gizmos.png image I have, and you can see that the arrow sprite is just literally an arrow, and then there's a square which we'll use for like the free transform, whatever. And you'll also notice they're white. That way we can tint it whatever colors we want and not have to worry about that. You'll be able to grab this at the link in the description, check it out, and you can get this picture, or you can use whatever picture you want. Just make sure that you do place it inside of our assets directory. This is important. You need to have an assets directory with the images, and make sure your file paths are correct, because otherwise you will have problems if you can't find the correct file. Okay, so we will get that arrow sprite, which is part of that sprite sheet, and we'll just pass it in here, and then we'll say this.x-axis object equals prefabs.generate sprite object, and we'll just use that arrow sprite, and I think it's 1648 is the size we're going to use. So we'll say 16 by 48. That is its actual height and stuff. So just make sure you have that right so that you don't get any weird stretching. And then we will do another one for the y-axis object, and we'll say 16 by 48 as well. Then we'll say this.x-axis sprite equals the x-axis object dot get component sprite render dot class. And then same thing for y-axis sprite equals y-axis object dot get component sprite render dot class. All right, a lot of code duplication in this. It could probably be avoided, but it's enough. It's little enough that I don't really care. Okay, and then lastly, we will add these objects to our scene. So we'll say window.getScene to add game object, and then we'll add the x-axis object, and I'll just duplicate that, and then y-axis object as well. So we create game objects, we add them to the scene. That's a good first step. They take in a sprite, so they're going to have some sort of sprite. Now we basically just want to make sure that it gets put in the position of the active game object whenever there's an active game object, right? So we'll go at override, public void update, take in delta time. Then we'll basically just want to say if this.activeGameObject does not equal null, we'll just set the gizmos to the object's position. So we'll say this.x-axis object.transform.position.set this.activeGameObject.transform.position, and then duplicate that, and we will do the same thing for the y-axis. Now clearly this is not going to be the correct location because they'll be overlaid right on top of each other and everything. And we'll see how to get around that in just a moment as well. Now we'll also need a couple functions that will just be helper functions to set it as active and set as inactive. And so we'll just take in a game object, and we'll say this.activeGameObject equals object, and then we'll just say this.x-axis sprite dot set color, and then we'll set it to the x-axis color. This.y-axis sprite dot set color to the y-axis color. And then when we set it as inactive, we basically just want to make sure that they are invisible. So we'll set the opacity to 0. So we'll say set inactive, and then this will just say this.activeGameObject equals null, thus making sure that we're not replacing them and stuff. And we'll say this.x-axis sprite.set color, and then we'll just say 0, 0, 0, 0. Well, we can't do that. We have to pass in a vector 4. So say new vector for f 0, 0, 0, 0. And then I'll duplicate that, and we will also set the y-axis. Control D to duplicate, by the way. All right, so we have these helper functions and everything, and this looks pretty good. Let's go into our level editor scene and get it set up so that we can at least have it sort of working. All right, so inside our level editor scene, I'm going to scroll down to where we're loading resources, and we're going to have to load the sprite sheet that we just created. So I'm going to say load sprite sheet, asset/images/gizmos.png is the location to mine, and we're going to say this is a new sprite sheet. Asset pool.get texture. We really need to change this too because this is a mouthful. Same path. And then we will also give it the sprite width, which is 24. The sprite height is 48. And the number of sprites is 2 and spacing is 0. In my case, you may have a different sprite, in which case you'll just do it as appropriate for your image. Then we're going to go ahead and actually move these two things all the way to the top of this function, because we will need the sprite sheet image when we go to create the sprite sheet object. So I'm going to go ahead and say sprite sheet gizmos equals asset pool.get sprite sheet, and just the same path again, images/gizmos.png. Now that we have the sprite sheet, we can actually add it to our level editor stuff component or game object. So we'll just say add component new gizmo translate gizmo, and then just pass it the arrow sprite, which is gizmos.getSprite1. Okay, cool. So now we have it added to our scene. It should be working, sort of. And our level editor stuff is being updated right now, and we will also add it in to be ImGui, because we will need that. So I'm going to say ImGui.begin, and then I'm just going to say level editor stuff. Then we're going to say level editor stuff.ImGui, and ImGui.end. This is just because we'll be using this for debug stuff. You can remove this at some later point too. Okay, so if we run this now, we're just going to get no errors, but nothing's really going to happen, and we don't really see the gizmos because we don't know what's happening. And this is our level editor stuff too. I didn't realize that we would have all these other things available to us too, which is kind of cool. But yeah, and so you can see we'll even be able to edit the colors and stuff. Okay, that's besides the point. Anyways, let's go back into our thing and actually make this work. So right now, how do we get the active game object? Well, the active game object is set in the properties window whenever you click on something. So I'm going to create a function in here and say public game object get active game object and just return this active game object. This is definitely not the best way to do this, but it's the easiest way to get this to work right now. Then we'll just go into here and we'll create a dependency. We'll say this takes in a properties window, and we will just say up here, private properties window. We'll just take a reference to that and then set it in here. So we're going to have to hook up this dependency in just a second, but this way we actually at least have a reference to it. And then inside of our update method, we can just say if we can say this.activeGameObject equals this.properties window.getActiveGameObject, and then we can just say if this.activeGameObject does not equal null, then this.setActive, and then we don't even need to pass it in at this point because it's already there. So we'll just get rid of that, and then we'll say else this.setInactive. All right. So now basically what we're doing is we're just getting the active game object from the properties window, and then if it's not null, we set it as active. If it is null, we set it as inactive. So this should sort of set it in the correct location. Let's go ahead real quick too and override the start method. We'll just say public void start because we will need this in a minute too. So we at least have that there. Okay, now let's hook up the dependency for the properties window. So if we go back into level editor scene, we'll notice that it says that we have an error because we're trying to create this, yet we don't really have the properties window. So I'm going to go into here and then just say window.get window or get.get properties, or actually we'll say .get ImGui layer.get properties window. And this is why this is not good. Like, you shouldn't be creating functions like this. And so this is how you know this is a bad design. But until we get an event system, this is the best way to do it. So to be continued once we get an event system. Let's go into our window class now, and we'll go down here and just create a public ImGui layer, get ImGui layer, return get.ImGui layer, and this will be static. Okay, so now that function is done, and then we'll go into ImGui layer, and we'll say all the way at the bottom here, just create a getter public, and this will be the properties window. Properties window, get properties window, return this.properties window. All right. And then if we go back into level editor scene, this should be good. So if we just change this from window.get to window.get ImGui layer, .get properties window. Okay. So we're all good there. And we just have to make sure we're passing it into the right place. And I'll move this parenthesis. So now if we run this, we should see that if we click onto an object, okay, yeah, you see we get the green arrow and the red arrow is behind it, but we can't really see it. So it moves to where we're clicking, but we need to rotate these sprites now. So like I said, we have to modify our render batch to allow rotation and our transform class. I can't believe that I did not do this because this is a really important part. So let's go into transform class, and then we'll say public float rotation. We're going to add a rotation, and it's going to be initially set to 0. Then we will go into our render batch, and we will fix this up to actually use this rotation. So inside of our load vertex properties method, we'll multiply by the transformation matrix if we need to. So we'll say boolean is rotated equals sprite.gameObject.transform.rotation does not equal 0. So if it's not 0, then it is rotated. Then we'll say matrix for f transform matrix, and we're going to just set this to the identity matrix for now, and then if it's rotated, then we'll construct the actual matrix. We'll say transform matrix dot translate by the sprite's game objects transforms position. And this actually needs to be 3 numbers because we need a vector 3 for a transform matrix. So then we'll just say sprite.gameObject.transform.position.y. And then if we look at the parameters, it expects a z and a w, which I think, oh no, we can leave out the w. So we'll just do X, Y, and Z. And make sure you do translate, not transform. Okay, so then we'll say transform matrix dot rotate, and we want to do float math dot to radians. So we're going to convert the degrees to radians. If you have it in radians initially, then just leave it there. So we'll say the rotation of our sprite object, and then you'll see that this also expects an axis. So we can just say 0, 0, 1, rotate it about the z-axis. That way we get the 2D rotation. And then we want to scale it, so we'll say transform matrix.scale, and we'll scale it by the sprite's transform scale x. sprite transform scale transform game object transform scale y, and z will say 0, and then for w, or we don't have to worry about w again. Okay, and actually I'm going to do z as 1 just so that we're not getting any weird numbers in that transformation matrix. Okay, so now we have a transformation matrix if it is rotated. Now we will go into where we actually load the position right here. So this is the only thing we really have to change. So what I'm going to do is I'm going to say vector for f current pose equals a new vector for f, and then I'm going to go ahead and copy this big line. So copy that whole thing, put it in there for the first parameter, then copy this one, and then put it in there for the second parameter, so x and y, and then we'll do 0 and 1. All right, so basically we're just putting this into the x position of this vector, this into the y position of the current vector, and then we're setting z to 0 and w to 1. Then we'll just say this is current pose.x, and this is current pose.y. Okay, so we're just sort of refactoring a little bit there, but this will make it easier if it is rotated. And I'll move this stuff down here too, just so you guys can see that. Okay, then we'll say if it is rotated, we have to actually multiply this position by the transformation matrix. So we can simply do that now just by saying current position equals, and then we'll say new vector for f, x add, y add 0, 1 dot multiply by the transform matrix. All right, so basically what ends up happening is if it's not rotated, we do the exact same thing we did before. But if it is rotated, then we just get x add and y add, which are these, and then we transform them according to this game object's position, scale, and rotation, which will give us the correctly created coordinates and everything. So it's simple, it's kind of dirty, but it works once again. So this should give us rotation, okay? Let's see if it works by going into our translate gizmo now, and then inside the start method, we'll just say that the x-axis object dot transform dot rotation equals 90 degrees. So if we do that, we should see it rotated 90 degrees. And if I click, we are not getting that. So let's see what's going on there. Oh, and that's because the start method is never being called. Let's go into level editor scene real quick and make sure we actually call this start method. So this is part of the level editor stuff object, which isn't part of the normal object. So after we init everything, we'll just make sure that we call level editor stuff.start. Okay, now if we run this again, we should see that it hopefully works. So, okay, there we go. It is rotated. It works. That's good. You'll also notice that it's saving these, and that's a problem we'll look at in just a minute too, which we will fix. Anyways, let's fix the y12 just so that that is pointing the right direction. So inside of the transform gizmo, translate gizmo, we'll just say this dot y-axis object dot transform dot rotation equals 180. So we'll flip that upside down, and now there we go. We get it saved. Okay, now speaking of these weird things, why are they sticking around? Well, notice, so if I go over here, I exit, when I come back, we have another one, and it's right there. And then I click, and it starts moving around again. What's happening? Well, it's being saved. Why is it being saved? Because we added it to the scene. So it's just automatically saving these objects, but we don't actually want to save these objects. So we're going to create a new function called set no serialize. So basically we can say set no serialize on an object, and this will make sure that it does not get serialized. So we'll just go into game object real quick, create this function, scroll all the way down. We'll just say public void set no serialize, and we'll say this dot do serialization equals false. Then we'll go up to the top, create a private boolean do serialization equals true by default. So by default, all objects are serialized. You can tell it to not serialize objects though. And then we'll just go ahead and say public void do serialization. And then we'll just say return this dot do serialization and make sure that we return a boolean. Okay, cool. So now we have to actually make it so that it doesn't serialize things if we don't want to serialize them. So we can go into the scene class, and inside of our save exit function right here, what happens is we automatically just serialize all of the game objects. So we want to say no, we just want to serialize game objects that want to be serialized. So we'll go over here and we'll just say list of game objects, objs to serialize equals a new array list. And then we'll just say for game object obj in this dot game objects, if obj dot do serialization, then we'll say objs to serialize to add obj. Then instead of serializing the game objects, we'll just serialize the objects that we want to serialize. So we'll say serialize objs to serialize. This should fix our problem. If we go into here and then say we created Gizmo there, if we go back in, then you'll notice that that was not saved. Okay, cool. So that fixes it. How do we get rid of all the ones that did accidentally save? Well, we can just go into our level.txt, delete that, rerun this. Okay, so now we have nothing, but if we add stuff in, we will go ahead and add a few objects, and then we'll just click on one. If we reload, then we'll notice that it did not save that. Okay, there we go. So that's fixed too now. Now we have to do just a couple more things too. Also, notice what's cool. If we just tweak this, it's actually tweaking the object. And I don't really like the way that it changes so fast, but you can actually tweak the colors and stuff right up here. So if you want to change the colors and see how it looks, then you can do that. Okay, anyways, we want to make sure that these are lined up correctly. So we can do that very simply. Just go back into the translate gizmo. And then we'll just create two more variables. We'll say private vector to f, x-axis offset equals new vector to f. We'll say private vector to f, y-axis offset equals a new vector to f. And then we can go down here and just right after we add the position, we'll just say this dot x-axis object dot transform dot position dot add, and then we'll say this dot x-axis offset. Copy that, and then we'll do the same thing for y's and for y there. So this will just add an offset to the position. So now if we go back in, we'll notice that it looks the same, but we have those variables should pop up. Okay, so the variables do not pop up. Why is it not showing the vector 2? Well, that's because if we go into our GameObject.ImGui, so if we just go into GameObject, or no, if we go into component, and then we go into the ImGui method, okay, here we go. So this is why it's not showing up, because we have type equals int, float, boolean, vector 3, vector 4. We do not have vector 2. Let's add in vector 2. So we'll say else if type equals vector2f.class, and then I'm going to go ahead and just bracket that, delete that, and fix this formatting real quick. Okay, and then if it's a vector2f class, I'm just going to copy this, and we'll say vector2f val equals vector2f value, and then we will just get rid of that, and change this to a drag float 2. All right, so this is inside a component. Now if we go back in, we should be able to tweak those. Okay, cool. So now you'll notice that it says y-axis and x-axis offset. So if we move this, you'll notice that's actually moving the x-axis in there. And then I'm going to move the y-axis up and just find a place that you like. All right, and so I think it looks pretty good there. And you'll notice that it will now retain that position no matter what. So this is just a quick and easy way to sort of debug your stuff. So 64, -5, 15, 61. We'll go back into our translate gizmo, and that was 64, -5, 16, -1, something like that. Check and see if that looks right. Okay, that's another problem we're going to have to fix in just a minute. Why did it fly away like that? We'll check it out in a minute. Okay, so change that to 60, 16, 60. Oh, that must have been 61. Okay. So that's good. Now, why is it doing this weird thing? If you click and hold the mouse button, it kind of glitches and then flies away. Why is it doing that? That's the last thing we have to fix, and that's just because if we go to our properties window, and when we're setting it, we just say if mouse button down. We don't actually have a debounce time in here. So we'll just add a debounce. So we'll say float debounce time, or float debounce, and I'm going to set that to 0.2f, so 0.2 seconds. And then we'll say if, or we'll say debounce minus equals dt, and then we will just add in and debounce is less than or equal to, or just less than 0. Then inside here, we'll say this dot debounce equals 0.2f. Okay, so adding in that debounce will just make sure that it doesn't glitch back and forth. And so if we click on these, it does it. And if you click and hold, then there is no glitching. The reason it was doing that was because it's sending out an event every single frame. And so it was just bouncing back and forth because it was setting it to null, then setting it to not null. So yeah, this works good. The debounce works, and we have our gizmos. All right, so this episode was kind of long. They've all been kind of long lately. Sorry about that. I hope you guys enjoyed it. If you did, please hit like and subscribe. And once again, just thank you for getting us to, we're at 750 subscribers now, just about. So really cool. Thank you so much. Sorry about the lack of videos too. I've been having some PC troubles this last week and had to install a new cooler and everything, which was a big hassle. But I should be good now. So in this episode, what we will be getting done is the scale gizmo and the rotate gizmo. So we will be getting both of these completely functional. The previous episode was sort of setting up the base technique, and now we will set it up so that we can actually move them, and then we can switch to scale mode, and we can also scale objects up and down. So this is obviously a really good point to be at with our engine, because now we can move our objects around. And we have some more steps to take to make it a more workable engine, but this is definitely a really big leap forwards in terms of getting things done. So in order to get this done, we will have to do a few different things. One of the things we'll be getting done is getting our drag listener working inside of our mouse listener so that we can actually get drag events and sort of deal with those appropriately. So we'll take a look at that first, and then we'll go ahead and actually implement the scale gizmo and the translate gizmo. So let's get started. All right, so how do we actually tell how far to move an object based on when somebody clicks a gizmo? Well, the answer is actually relatively simple. So if somebody clicks onto one of the gizmos, say they click here, and they click here at frame 0, okay? This could be any frame. It doesn't really matter what frame it was. Now let's exaggerate the movement. Say the next frame, the mouse position is over here. So this is frame 1. And this is highly unrealistic because moving the mouse from here to here in one frame just most likely will not happen. But we're just exaggerating it for illustration. So if the mouse is here, frame 0, and actually let's make this a little more complicated. Let's say the mouse moves down to here at frame 1. So the mouse clicks onto the gizmo, it's still holding down, frame 1, it's over here. How far do we move the object? Well, that's simple. We just move the object this X distance, right? So whatever this, I'm going to call this delta X is, that's how far we move the object, right? So how do we get that delta X in the frame? That's pretty simple too. We just calculate how far the mouse is moved in X distance only between frame 0 and frame 1. So we could call this X, Y, and that'll be like X0, Y0, and this will be X1, Y1, okay? So we track what the X's position was in frame 0. This is what the mouse's position is now. How far do we move the object? Well, we just add X1 minus X0 plus, and we'll call the object just G, X position, right? So the game object's new X position is just equal to X1 minus X0 plus the game object's position. And intuitively, that makes sense. We're just moving at the distance that the mouse moved in the X coordinates. It really is this simple. There's no hidden gotchas or anything when it comes to this. And so we just have to calculate how far the mouse has moved in the X coordinates between frames, and that's how far we move the object, okay? So how do we scale it then? Say these were scale arrows instead of regular arrows. I'm going to blow your minds here because it's literally the same thing. It's just the scale of X would be X1 minus X0 plus the original scale of X. Now you might actually factor this. So what I did was I actually had a scale for the scale. So instead of just doing X1 minus X0, I multiply by some factor. We'll call that F. And then I add that to the scale's position. And this factor is just some number less than 1. And the reason I do that is just because if we do this big of a scale change, usually that's bigger than what you would want. You would want it to incrementally go. So if you do like 0.5 and just multiply those by it, it'll just scale it slower or faster. It's basically the speed, the sensitivity, if you will, sort of like we did with mouse sensitivity. Now this is all good and stuff, but right now we have no way to detect mouse dragging accurately in our game engine. So we are also going to implement proper mouse dragging. Now, how do you tell the mouse is dragging? Well, that's actually not too bad either. the way you can tell that the mouse is dragging is, say the user clicks down and at least one mouse button is down and you get a mouse move event. So it's currently pressed some button and it has moved, then this is now a drag event and no longer a click event. So let's go ahead and implement the mouse dragging, and then once we get mouse dragging implemented into our mouse listener, we'll go ahead and implement the whole scaling and translating gizmos. Okay, so where we last left off last episode was we just had these gizmos pop up whenever you click onto one of the objects in the scene, and now we want to actually make them work and not fly away, which I said we fixed, but we didn't, and there's an actual reason for why they fly away like that. So we'll take a look at that and make sure it doesn't happen anymore as well. So the first thing we're going to implement is we're going to go ahead and go to the mouse listener class and actually get the whole drag working, and then the get dx and get dy working as well. Well, actually, these do work fine still. It's just the dragging is not working. So right now what we're doing is we're just saying if we pressed, then basically, well, actually, it just looks like we never set dragging to true. We just set it to false. So we will fix that. Now we are going to add a couple more variables in here just for some help with getting positions in world space. So I'm going to go ahead and define some more variables up here called world x, world y, and then last world x and last world y first of all. And so these are just going to be the same things as these, just calculated in world coordinates, because currently if somebody asks for, if we go down to here, the get ortho x and get ortho y, which is basically get world x, we calculate it on the fly every time. And this is bad because what if somebody asks for it multiple times in a frame? We don't want to recalculate it. So we should have done this a while ago, but we didn't. So now we are doing it. We're just going to go into here and say private static void calc ortho x. And then we're just going to copy all this, paste it into here. And then we're going to say get.ortho x, or actually world x equals current x. So we basically just do that, and we could actually copy this and paste it over that and then get rid of this line completely. So now we have a calculate method, and then what we're going to do here is just say return get.worldx instead of orthox, and then we'll go ahead and do the same thing for, and we have to cast that to a float too. So just cast that to a float, and then we'll do the same thing for ortho y. So we'll just go ahead and create a public static, or actually this is private, static void calc ortho y. We will copy and paste all of this once again. And then right here, we'll just say get.world y equals temp.y. And then we can go ahead and remove all of that. Then right up here, we can just say return get.world y, and we'll cast that to a float. Okay, so that's just a little bit of refactoring, but this is good because now we can make sure that we only calculate once a frame, and then if somebody asks for it, we get it. All right, and so when should we calculate the world x and world y? Well, we'll calculate that every time the mouse position callback is called, because this means the mouse has moved. This way, we can just make sure that we get the correct position every time we call those functions. So what we'll do is we'll just say get.lastWorldX equals get.worldX. So we will just track the last positions so that we have access to those if we need them. And then like we have right here, we will just go ahead and say calculate ortho x and calculate ortho y. So this will basically just do the same thing these are doing, which is saying, hey, calculate the new position with the new expos. Make sure you put these below this too, since it uses these values. Then we're going to remove this get.isDragging equals blah, blah, blah. That's what we were using to calculate dragging before, and it does not work good at all. So the way we can calculate whether or not we're dragging, like I said, is if they click down and then they move the mouse, that is a drag. If they just click down, but they don't move the mouse, then that's not a drag, that's a click. So how do we check and see if that's happening? Well, I'm just going to add a new variable up here, private int mouse buttons down equals 0. So this is the number of mouse buttons that are being held down. And so then we will go to the mouse button callback every time a press is hit, we say mouse button down plus plus. And every time a release is hit, we say minus minus. So when this is 0, the mouse button's down, then this means there are no mouse buttons being pressed. When it is greater than 0, it means there's a mouse button being pressed. So we can just go up to here, and when the mouse is moved, we can say if get.mouse button down is greater than 0. If we have one mouse button that is being down and we just moved the mouse, then that means we're dragging. So we'll say get.isDragging equals true, and that should be good. And then how do we know that the drag has ended? Well, we can just do the same thing we were doing before, where if the mouse button is released, then we'll say get.isDragging equals false. Technically, we could put something like equals get.mousebutton down is equals 0, I guess. But I'm not doing that because if they hold down like 2 buttons at the same time, I'm not sure when I consider that an end drag and everything. So we'd have to look more into that stuff. But for now, this is fine. This will calculate when we get a drag and when we don't get a drag. Then we're going to go down here and we're just going to make some similar methods to these. We're going to say public static float get world dx. This will do the same thing as this function. It will just do it with the world positions instead. So we'll say get last world x minus get dot world x, and then we'll do the same thing for dy. So we'll just copy and paste this. And we will remove that and change this to y and change this to y. All right. So this way we can get the world dx and then get the world dy, which should help us out. Now we can check and see if this is working very quickly. We'll just go into the translate gizmo in the update function. We'll just say if mouse listener.isDragging system.out.println dragging. So now if we go into here, we should be able to drag. And once we start dragging the mouse, it'll say dragging. And so if I go into here, yeah, you'll notice it says dragging down there. But if I click and I hold and I don't move the mouse, it doesn't say dragging. Okay, so that works good. Now we have a method to check and see if the mouse is in fact dragging. Now that we know that, we need a way to tell if the mouse is over the gizmo or not, so that we can tell if we're hovering over the gizmo. So I'm going to go into the gizmo class and we're going to declare just a couple more variables. We're going to call this int sprite. Or actually, I'll call this gizmo width, which equals 16. That's the width of the gizmo in world units. Gizmo height equals 48. That is the height of the gizmo in world units. This is important so that we can tell when the mouse is inside the gizmo. And then I'm just going to go down here. And first of all, I'm going to move this whole this.activeGameObject equals null thing to below this whole thing. And then basically, if it's not null, then we're just going to return here. So basically, if there is no active game object, we'll just exit early instead of going on with the function. Then I'm going to go ahead and we'll go up here and we will say boolean x-axis hot. So this is the x-axis gizmo, the little red arrow that points to the right. And I'm going to say equals check x hover state. So this will basically just check whether the mouse is hovering over the x-axis gizmo. And then we'll say boolean y-axis hot equals check y hover state. And these are going to be very similar functions, basically the same. And they're just going to check and see if the mouse is hovering over that specific gizmo. So we're going to say private boolean check x hover state. This will just check whether the mouse is hovering over the x-axis gizmo. So we'll say vector 2f mouse pose. And this is the mouse position world coordinates is new vector 2f mouse listener dot get ortho x mouse listener dot get ortho y. And then we can just say if mouse pose dot x is less than or equal to x-axis object dot transform dot position dot x and x mouse pose dot x, and I'm going to move this to a new line. We're going to say is greater than or equal to x-axis object dot transform dot position dot x minus the sprite height, or actually this is gizmo height, sorry. And this is why we're separating it into two functions, is because the x-axis object is actually longer than it is tall. And so we said gizmo height is 48, but technically that's the width of the x-axis gizmo. So we just separate it into two functions so that we can check these separately. Then we'll say and mouse pose dot y is less than or equal to y-axis object dot transform dot position dot y, and mouse pose dot y is greater than or equal to y-axis object dot transform dot position dot y plus sprite width or gizmo width. And I think I have these backwards. This should be greater than, this should be less than, and these two should be all right. Okay, so this basically just checks and see if the mouse is inside of the width and the height. It's a simple box detection. I've got some more videos that you can check out for more information on how box detection works, but basically a point inside a box just means that the points x is less than the box's right x and greater than the box's left x. y is greater than the top y, less than the bottom y. And that's exactly what we're doing. Okay, so if all this is true, we're going to say x-axis object or x-axis sprite dot set color, and then we want to set the color to the x-axis color hover. So we just set the color, and then we will return true. Otherwise, we'll say x-axis sprite dot set color to x-axis color, and then we'll return false. So if we are hovering over the sprite, we set it to the color hover. Otherwise, we set it to the regular color, and then we just return whichever of those it is. Now let's go ahead and check the y hover state, which is very similar. So we'll just say private boolean, paste that. I will copy all this, and then we will change the things appropriately. So we just want to make this minus the gizmo width now, and we want to make this minus the gizmo height. And then we just want to swap this to a less than or equal to and swap this to a greater than or equal to. The way I found these, I just sort of messed around with it because with the rotation stuff, it does throw things off a little bit. So I just messed around with the greater than, less than, or equal to signs, and then the plus and the minus to get it exactly right. Okay. Then we'll say y-axis sprite and just change this to y-axis color hover. So y-axis color hover, and then we will change this to y-axis sprite and change this to y-axis color, not hover. Okay, so now if we run this, we should see that when we hover over either of these, it should change. Okay, so we're getting that. That looks like it's in the wrong place completely though. Oh, and I see the problem here. So I changed this to y-axis object. This should be x-axis object, and this should be y-axis object because we're checking the objects and I sort of swapped those around for some reason. Okay, so now if we run this, okay, there we go. So when I'm hovering inside of either of the gizmos, they change to their respective color. And we can actually change that color real quick too, just to make it a little bit better. So the colors I am using are for the non-hover, I use 0.3F, 0.3F here, and then I just go 1001 for the hover. And then I do 0.3F here and 0.3F here, and then just 0101. So that gives it just like a dark tint when you hover over it instead of going completely black. So there we go. You notice that when I hover over them, they get a little bit darker. You can tweak it however you want, and that should be fine. Now we need to make it so that it doesn't do that. First of all, well, actually, yeah, we need to do that first. So let's make it so that it doesn't fly off. First of all, why is it actually flying off that way? Well, if we go to the properties window, what happens when we click down on any object? Well, it gets the ID of the game object, and then it sets the active game object to that ID. Well, what just happens when we click on the arrow? Well, we click on the arrow, and then it sets the active game object to the arrow, so it's constantly trying to position itself in front of itself, and then it ends up flying away like that. And so we need to fix that, and that's pretty easy. We can just fix it by basically saying, hey, set the active game object as long as it's not one of the gizmos. Or in the case of what I did is I did this thing where I said new Java class, and I call this non-pickable. And we're just going to say this extends component. This class does absolutely nothing. Okay, it's just there for us to go into here and then say game object picked object equals, and then we will just copy and paste this. And then we'll say if picked object does not equal null and picked object dot get component non-pickable dot class does equal null, only then will we set the active game object to the picked object. Otherwise, we don't. So then we'll say else if picked object equals null and not picked object, and we're not dragging right now, so and not mouse listener dot is dragging, then we will say active game object equals null. So basically we just check and see if that object has this non-pickable class. If it does, then we will not set it. Now this isn't going to fix it immediately because if we go in, we'll click onto it and it'll still fly away. So we can fix that by going into our translate gizmo. And then when we go ahead and add these objects, we'll just go down here and we'll say this.xaxis object.add component non-pickable.class, or actually a new non-pickable. And then we'll say this.y-axis object.add component new non-pickable. All right, now if we go into here, since they have the non-pickable class, it doesn't trigger it when we click on these, but it does trigger it if we click on anything else. Okay, so now they're not flying away anymore, and we can correctly start doing the drag events and actually using that. So if we go back down to the update method, we have this whole x-axis is hot, y-axis is hot. So now we know whether we are hovering over the x-axis or the y-axis. And we can say if x-axis is hot and mouse listener.is dragging and mouse listener.mouse button down, and we'll say GLFW mouse button left. So if they're dragging the left mouse button, and then just click onto here and hit Alt Enter to import that static constant. So if the x-axis is hot, we're hovering over the x-axis gizmo and we're dragging the mouse and it's the left button that we're dragging. Then we're going to say x-axis active equals true, which we don't have yet, and y-axis active equals false, which we also don't have yet. So let's add these real quick. These are basically just saying, okay, we're actually in the midst of dragging these. Okay, so hot just means that we're hovering. Active means we're actually dragging. We're interacting with the component or the gizmo. And then we'll go up here and we'll just say Boolean x-axis active equals false. And then I'll duplicate that and say y-axis active also equals false. So now we can go down here and then we'll say, we'll go up here and we'll modify this a little bit. We'll say if it's hot or it's active. So if it's hot or it's active, then it's just active. And if the mouse listener is dragging and the mouse button is down. Then we'll say else if y-axis is hot or y-axis is active and we're dragging the mouse and the mouse button is being pressed, the left mouse button. So if all this is true, then y-axis is active. So we'll set that to true, and x-axis is not active. So we'll set that to false. So this way we just know which one we are actually interacting with right now. And then if none of that is true, then we'll just say x-axis is active is false and y-axis active is also false. So neither of them are active if we're not dragging and actually holding on to either of them. Okay, so we have a bunch of stuff in here, and I'm going to do something that's going to blow your guys' mind. Maybe not. But I'm going to go ahead and say, let's refactor this whole class. So we're going to go into here and we're going to create a new class. I'm going to call this Gizmo. All right. So this is just going to be a generic Gizmo. And inside of this Gizmo, we're going to create a constructor that basically looks the same exact as this. Actually, it's all going to look so similar that I'm going to go ahead and just copy all of this. And then we're going to go into Gizmo and we're going to go paste everything. And I'm going to hit OK to import those. Then we're going to say this extends component. And we're going to change this to Gizmo, the constructor, so that it matches. And we should have no errors in here. Okay, cool. We have no errors. And then I'm going to go ahead and I'm going to make the active property protected. And I'm going to do that for both of these. And then I'm also going to make the active game object protected. So we have this protected, protected, protected. Cool. Now, what does this do? This isn't really cool. Well, it actually makes it so that we can make more gizmos really easily. So I'm going to just change this to this extends gizmo instead of extends component. Then I'm going to go ahead and delete all of this. We don't need any of it. We can leave that in. And then what we're going to do instead is we're going to go in here. We're going to say super, and then we're going to call our parent constructor with the same parameters. So we just make sure we call the same parameters. We're good. I'm going to go ahead and delete all that. And we can actually delete all this too. So we can basically delete almost everything inside this class, which is really nice. And then delete all of this too, because we've moved it all into its parent class. So we still have all the functionality in here that we had before. It's just inside the parent class. So now if we go into, well, if we just run this, it should still run the same because we didn't lose any of the functionality. So if I click onto here, oh, and we have to make sure to call super.update too. So make sure to call super.update inside the update function. Now, if we go back into the game and we click this, okay, there we go. So you can see we still have all the functionality. We're just refactoring. Now that we have this though, we can go ahead and say if active game object does not equal null, and then we'll say if x-axis is active, we're dragging the x-axis gizmo. And then we'll just say active game object dot transform dot position dot x plus equals mouse listener dot get world dx. And let's see if this works properly. So now if we click onto the object and we click, okay, so it's working. I'm just doing it backwards. So we need to change that to minus equals. And then we'll do the same thing with y-axis active. Then we'll say active game object dot transform dot position dot y plus equals mouse listener. I think it is plus for this one. Dot get world dy. All right, so now if we run this and we click onto the object, we can move right and left, and okay, y was messed up too. So we need to change this to minus. But look at how easy that was. So now that we have all that functionality inherent in the parent, it was very simple to just do this and just drop in those couple of lines of code, which makes it so that now we can move it the correct way. And you'll notice that we're getting some problems, like if I go up here and then I accidentally hit the x-axis, I switch to that one, so we can fix that. And we're also getting some weird lagging errors. So first of all, we can fix the weird lagging errors just by moving that down. Basically, if we update after we move, that ensures that the gizmos are in sync with the game object, whereas before they weren't. So now if we go back, click onto this, moving up and down, it sticks with the mouse, which is good, but I'm still getting some weird errors for the X position, and that's actually caused by something in our mouse listener. So go back to mouse listener real quick. I believe it's happening because if we go back to end frame, we actually have to do this thing that we do with the last X's with the world X's as well. This just makes sure that if we don't move the mouse, then the DX will reset itself essentially. So I'm just going to change all this so that we're matching the other one. All right, if we go back in, we should get rid of that error now, and then there's just one more we have to fix. So now if we go, we are perfectly fine when we move them, but if I move up and down really fast and I hit the red arrow, then it switches to that. We can fix that too, just by going into the translate gizmo and saying if x-axis is active and not y-axis is active. Okay, that should fix everything. So now it should just work. And you can see if I click onto here, click the Y, I move it, click the X, I move it. That's pretty awesome. It's not that hard to do too. Like we can literally just go into here and write a couple lines of code. Now let's do the same thing for scale gizmo, okay? So I'm gonna go into here and say new class scale gizmo, and I'm gonna hit enter. And then I'm just gonna copy and paste all of this right into scale gizmo. And then I'm just gonna change this to scale gizmo instead. And we're going to change this to scale sprite. So we want a different sprite passed in as well, which should be good. We're going to say this extends gizmo. That way we get all of our functionality. And then instead of doing position.x, we're going to do scale.x and scale.y. It really is this simple, okay? Except we will have one more problem that we'll see in just a minute. So first of all, though, let's go ahead and go into our level editor scene. If we go into here, we want to just make sure that we add in two more components to this. So we add the translate component. Let's go into level editor stuff and we'll say add component, new scale gizmo. I'm going to go ahead and say it's gizmos.getSprite2. And then we're going to say window.get ImGui layer.get properties window. And the way that we're going to do this is I have another sprite that I will give to you guys in the download link so that you can get the proper sprite. And then just go down to the gizmos.png and then change the number of sprites to 3. And you should have the scale gizmo included in there too, or the sprite, so that we get the correct sprite here. So just make sure you go into the assets directory, images, and get a new gizmos PNG image. That way you have the scale, and free move, whatever, and then the translate gizmos. So as long as you have those, you should be good. And then we can go and we'll click this. And you'll notice that we will get the scale gizmo as well. So we get the scale gizmo, but it's moving and it's scaling at the same time. Why is that? Well, that's because we have attached both the translate and the scale gizmo to the same level editor component. So if we remove translate, if we comment this out, then we'll just get the scale gizmo. And if we remove the other one, we'll just get the translate gizmo. But that's not really ideal. Ideally, we'd like to be able to just have both of them, right? So how do we solve this problem? We make a gizmo system. So we'll say add a new component gizmo system. And this gizmo system will take care of figuring out who should be updated when and everything. So we'll go ahead and we will actually move this into the gizmo system. Let's go into components, create a new class, call this gizmo system. We're going to say he extends component. And then we're going to go ahead and say this guy takes in a private sprite sheet gizmos, and so this could be the gizmo sprite sheet, and then we're going to say int using gizmo equals 0. So if it's 0, we're using the translate gizmo. If it's 1, we're using the scale gizmo, basically. Then we're just going to go ahead and say public gizmo system. This takes in a sprite sheet, sprite gizmo sprites. Then we'll say gizmos equals gizmos sprites. Then we'll go ahead and go and override public void start. And inside of here, we'll move those creation of those things into here. So we'll go into level editor scene. And where we have these, we're going to go ahead and copy that and then go back into gizmo system. Then we're going to paste that into here. And then instead of adding it to level editor stuff, we're going to add it to this game object. So we're going to say game object.add component, game object.add component. That should be good. Then we'll go down here and we'll say @override public void update float delta time. And we'll say if using gizmo equals 0. Then basically we just want some way to set it to say, hey, we're using the translate, not the scale. So if we go into gizmo, we will actually add in one more function to this, or two more functions. We'll say public void set using, and this will say this dot using equals true, which we don't have yet. And then we'll say public void set not using, and this will set this dot using equal to false, which we don't have yet. Let's go back to the top. Up here, we'll just say private boolean using equals false originally, and then we can set it to true. And then right up in our update method, we'll just say if not using, then return. So if we're not using this gizmo, we don't actually run the update method, which is how we'll make all this possible. Then inside gizmo system, we can say if we're using gizmo 0, we'll say gameObject.getComponent, translate gizmo.class.set using. And then we'll say gameObject.getComponent, scale gizmo.class.set not using. Then we'll say else if using gizmo equals 1. So if we're using the scale gizmo, then we'll copy paste this, and then we'll set this to not using, and we will set this one to using. So this way we only update one of them, whichever one we're actually using at the moment, and we will only draw whichever one we're actually using at the moment, because we'll go into here, and when we set it to not using, we will also say this dot set inactive. That way we can't see it, it's out of sight, out of mind. Now, how do we switch between the gizmos? We can switch just by checking for a key press. So we'll say if the key is pressed, and I'm going to set this to GLFW key E. And then I'm going to import that. I'm going to say using gizmo equals 0, else if key listener dot is key pressed, GLFW key R, then we will say using gizmo equals 1. So if you press E, you switch to translate. If you press R, you switch to scale. And I might switch this to W and E. I'm not sure what Unity and Unreal use, but I know they use something like that. Okay. Anyways, though, we need to go back into level editor scene because we have to fix one more thing, which is actually supply this with the gizmo sprites. So we'll just supply that. Now, if we run this, fingers crossed, everything should work. So if I click onto him, you'll notice we get the translate gizmos and they work fine. And if I hit R, then I get the scale gizmos and we're just scaling. And if I hit E, I switch back and you can go on and do whatever you want. Okay, though, that's it for gizmos. We'll add rotate gizmo in eventually. One other thing that I want to mention, I know there's this bug where if you add in a new object, the gizmos are behind it. That's because we don't have Z indexing. So Z indexing will be the next thing we'll cover, just so that we can actually get proper Z indexing working with our batches and actually put objects in front of each other. But that covers it for this tutorial. I hope you guys enjoyed it. If you did, please hit like and subscribe. They've been a little long lately, but this way we can get more stuff done at least. Stay tuned for the next episode when we'll be adding Z indexing, and then hopefully soon after that we'll be working on hopefully like text rendering or something, because it's about time we start adding those. Most likely we'll be working on the properties panel next and getting this up and running so that we can actually click on objects and change more than just their sprite render. In this episode, we will be working on the properties panel, and we will get the bug fixed where when you clicked on this, these were behind. We do have Z indexing support, I just did not know about it. So we'll be fixing this, and we will be working on this properties panel so that we will get this result that you see. And I'm not gonna lie, I took a lot of inspiration, like mainly all of the code from the Chernos tutorial. So there's a link in the description to the Chernos original C++ tutorial. I had to change a few things to get it to work right using the Java version of ImGui, but this is what we will be working on. And then we will also be making it so that if you have some other objects with other stuff, that all of their properties will be exposed properly and you can sort of open and close these things. So let's get to it. Normally I would do a little drawing tutorial, but I feel like most of this code is straightforward enough that we don't really need a visual explanation. Let me know if you guys need any extra explanation in the comments and I will try and resolve those. Okay, so first thing we're gonna do is fix this bug where basically when we place in a new object, the arrows are behind it, and that's because we have Z indexing, we're just not using it right now. So thank you, I cannot remember who commented, but somebody commented and told me that we do have Z indexing support. I was about to go ahead and rebuild it again, but we do have it, we just don't have it working for that. So I am going to do a little bit of refactoring. First, we're going to go into our transform class because really the Z index should be in here. So we're going to go ahead and create a new integer in here, and we're just going to call this Z index, which is pretty straightforward. And we just want to make sure that we go ahead and initialize this up here. We'll just say this.ZIndex equals 0 whenever we initialize a new transform. And then we also want to make sure that we update our equals method because it is now, we didn't update this when we added rotation too, but this should be, make sure that the t copy or whatever t dot rotation equals this dot rotation and t dot z-index equals this dot z-index. That way we can really tell if two transforms are the same. So we didn't do that when we did rotation 2, which may have caused you some problems, but this should be fixed now and everything should be good. So now that we have z-index inside of the transform, I want to do something else to sort of change things up a little bit. So if we go into our game object class, and we scroll to the top, you'll notice that we have this transform up here. I'm going to go ahead and mark this as transient. And then I'm also going to take out the z-index because we no longer need to do z-indexing through this. And then that means we can take it out here as well, which means we can also take it out here as well. And I'm going to go ahead and also take out transform from here. And you'll see why in a minute. Basically, transform should be a component. Right now it's not. If we go into here, it does not extend from components, but it should because that is what it is. So I'm going to make sure that this does extend from component and then hit Alt-Enter to import this. And then when we go back into game object, what we're going to do is we're going to make sure that the transform is always attached to game objects, right? So if you have a game object, it will always have a transform. Then whenever somebody needs to get a hold of that transform, they can get a hold of it through this reference right here, which will basically just be a direct reference to that component. So how do we make sure that we get this to reference the actual component and everything? Well, we do that in our deserializer. So when we are deserializing objects, instead of going through this and sort of implementing it this way, what we'll do is we'll say create the game object, then we'll just say go.transform at the end of all of our component deserialization equals, and then we're just going to say go.getComponent transform.class. Now, if you have a level already built, this will break things. So we're going to have to go into where you have your level file. So in my case, that's in C, Dev, Java, and I'm going to go to Mario YouTube, then delete this level.txt because this will break things a little bit. We're also going to remove these. We no longer have transform and z-index being serialized as part of the game object. And then we're also going to have to go into the game object serializer. I'm forgetting where that is. If we just run, if you hit Shift F10, we're going to get a bunch of errors and we can fix all these. So just click on the top one. Okay, first of all, we'll remove this function. We no longer have, actually, we can keep, well, yeah, we'll remove the function because it's cleaner if we don't have that. And then we'll go to the next error, which is in render. This is going to say we don't have a z-index. Well, we can just go transform.z-index now. That should fix that error. And then we'll get the next one, which is same thing, just different line. So then we'll do the same thing we did, just transform.z-index instead. Access that the way it should be accessed. And then, okay, in here, this is a good example of what we want to do. We do want to have a game object like this, but we want it to have a transform. Well, how do we get a transform? I'm going to do something else from the Cherno. So instead of creating game objects manually, what we should do is we should say, hey, whatever the current scene is, I want to create a game object, and this should return as a game object. So inside the scene class, we'll create a function called create game object, which will take in a string, which is just a name, and we'll eventually have this name exposed too. And then inside of here, we'll just say game object, geo equals a new game object, pass it the name. Then we'll say geo.add component, new transform. So this makes sure that it is built with a transform, and we don't have to worry about that. And then we will just say, we want to make sure that we assign that reference now. So we'll say geo.transform equals geo.get component, transform.class. This way, when the start method is called, we make sure that this reference is set. So if anyone uses the direct reference, they have that. And then we'll just return that game object. Then we will go back into where this error is coming from. And instead of doing it this way now, we can remove all this. Well, I'll keep some of it because we're going to actually need this part. So I'm going to copy that and then just delete the rest of it from here, paste it down here. We'll need that in a minute. And then instead of instantiating a new game object directly, we will say window.getScene .create game object, and then we use that name. And then we'll just say right down here block.transform.scale.x equals size x, because we can see that we were setting the scale right here. We can actually remove that too. And we'll say block.transform.scale.y equals size y. Now we have the same functionality and we won't have any sort of weird errors. And then if we run this again, we'll see we get another error. Let's see what this is. So once again, we have sort of the same problem. This is actually, we can just remove this. And since we don't want, well, okay, we're going to give this one a transform too, even though it probably could deal without one, but we'll give it one anyways. So we can just say this equals this dot create game object. And then that should get rid of that error. Okay, so now we have everything fine. Let's place something in the scene. Okay, cool. Everything still works the same. And if we move it, it still moves, which means our transform is getting set properly. Okay, so we basically just refactored a lot. And then let's just make sure that it is still working. If we reload it, we still see the object. Okay, cool. So that's all working good. Now let's actually do the one thing that we were going to do in the beginning, which is if we go into our gizmos, system gizmo.java, and then inside of the start method where we're setting the rotation everything, we will also say this .x-axis object .transform.z-index equals, and I'll set it to like 100. Technically we could set it to something lower, but this will just make sure that it will most likely be in front, and we can add in things in the future to make sure that these are absolutely in front. But basically we just say, okay, set the z-index to something really high. That way the arrows are always in front of the objects that we place in the scene. So now if we place in an object, the arrows are in front of it. Cool. That fixes that problem. Nice. Now we can move on to the properties panel. So how do we make this properties panel actually reflect all the properties nicely? You'll see that it's actually reflecting the transform, the position and scale now, which is good, but it's not really good looking. So we'll make it look good looking. So the first thing we'll do to make this look better is we'll go into our game object class one more time. Because first of all, what you'll notice is that if we click on an object, there's like nothing telling us what these variables are part of. So like rotation is clearly a part of transform, but how do we know that since it's right next to the sprite render's color picker? You know, we can't tell. So we'll add the headers, which are basically just the tabs to open up into a specific component. So to do that, we can just go down here and then we'll say, as we're iterating through the components, we will just go if ImGui dot, and then we can say collapsing header with a label, and the label will just be c.get class.get simple name. So we will just give it whatever the class is. So that means that if your component is called font render, it will just get that and use it as the name, and this will basically make it look a little bit nicer. So basically if we click onto this now, you'll notice that it says sprite render transform, right? And we have these little collapsible things that we can open and close. Cool. So that's part one done. Now part two is making these go on the left, all the labels, and then making these look nicer. So we can do that by creating some custom ImGui tools, and I am going to go ahead and say, let's go to the editor package, create a new class in here, and call this JImGui. I'm prefixing it with a J to basically notate that this is our extension. This is not ImGui, this is our extension, which J is for Jade, which I'm gonna have to change the name of that because it turns out there's another Jade engine out there. Anyways, this is basically where we're gonna place a bunch of static functions that do some extra stuff for us. And if you have seen the Cherno's video, which I did mention is where I'm getting my inspiration from, then what you're about to see should look very familiar. It will be slightly different though. So we're gonna make a public static void draw vec to control. and this will take in a string label, a vector2f. This is going to be the values with a s, and then float reset value and float column width. And that's a little bit long, but I'm going to leave it as is. Then we're going to go ahead and copy this because Java does not have default variables and we want to make sure that we can overload this. So we'll copy that once and then twice, and we will just remove 2 of these. This way you can call it using any of these. We sort of did the same thing inside of our debug drawing API. This will just call drawVec2control label value, and then it will use values. And for reset value, we'll use 0.0f by default. And I think I have this as 220 by default. And we'll actually go up here and just say private static float default column width equals 220.0f. Copy that, just paste it over this. Okay, and then we will copy this, paste it here, except instead of doing this, we'll say use the reset value that they pass in. So basically this calls this, and this also calls this, and they just provide some default values. It's basically the same thing as if we were to say this equals 0.0f and like JavaScript, but we don't have that in Java. So how do we want to draw a vector2 control? Well, we're going to be basically doing the same thing as Cherno, which he's doing the same thing as Unreal. So basically, instead of drawing it like this, we're going to have a button in front of this that says X, and then we're going to have a button in front of this that says Y, and we're going to have position the label on the left. The way we can code this is, first of all, we're just going to say ImGui.pushID, and then we're just going to push the label. This will just make sure, and then we're going to say popID, because we'll have to do that at the end. This will make sure that we don't get any like tool controls conflicting with each other because they have the same labels. So it's basically just ImGui's way of a namespace or a class name. Then we're going to say ImGui.columns2. This will give us 2 columns that we can use. So one for the label and one for the vector control. And then we're going to say ImGui.set column width 0 column width. So that will give it the initial width. And then we'll say ImGui.text label ImGui.next column. So what this will do is it will basically just do whatever label we pass in, and then it will create a new column. So the best way to see this in action is to just do it real quick. So I'm going to go into our transform class. So transform, and then override the ImGui function so that we can see this. So we'll just say right here at override public void ImGui, and then I'm just going to say JImGui dot drawVec2 control label position, and then I'm going to give it the this dot position. Okay, so now we can sort of see what's happening. If we run this again, I click on this, click on a transform. Okay, so you see that we get this position, and then we get this thing, which basically moves around, and then we get this on the same line. What is happening here? Well, if we go back into here, we're basically saying, hey, we have 2 columns, and then we put the label, which is what we passed in, right? We passed in right here, position, and then it goes ahead to the next column. And so if I was to say ImGui.next column again, and then we actually say ImGui.columns1, this will basically reset the columns at the end, then everything should look completely normal. So if we go back in and I click this, okay, so you see we have a column here, we have a little divider that's kind of hard to see, but you can move that around, and then we've got position, and then this is the next column, and then we got our next thing. Okay, cool. So now that we have the column in, let's draw the X control, right? So we just want to draw a button that says X, and then we want to draw like a drag float control. So to do that, we can do this thing, which is basically how ImGui does it and how Cherno did it, except we have to do a little differently in Java. So first of all, I'm going to say push style var ImGui style var.item spacing, and we're just going to set this to 0, 0. Then I'm going to say float line height, so we get the line height equals ImGui.get font size plus ImGui.get style.frame padding y times 2.0. Oh, and this should be get font size, not get font. Then I'm going to go down here and I'm going to say vector2f button size. So this is going to be like the X button is a new vector2f line height plus 3 line height. So we basically just create a vector2 with the button's size that we would like to be. Make sure that's a float. And then we're going to say float width each equals ImGui.calc item width minus button size dot x times 2. over 2. What the heck is happening here? Well, basically what I'm doing is we have some space left, right? So what I'm doing is I want to have 2 controls. Okay, well, this isn't going to work right now. We have 2 controls that we want to place, right? We have something like position, then we have a bar, and then we have some white space. We want to place 2 controls here. How wide do each of those controls have to be? Well, we have to calculate, first of all, how much space is here. So we calculate the item width minus button size.x. So how big are each of these buttons? Times 2, because we have 2 of those buttons. So we're going to have like a button here, then we're going to have a drag control here, then we're going to have a button, drag control. So we subtract out, we don't have this space left, that way we can get how big each of these are, so we just divide by 2. That's all we're doing. So that basically just gives us the width for each of those. And since we push the style bar here too, we also want to make sure that at the end we pop that style bar, because that is what was causing the problem. I'll do it before we do columns 1, 2. Okay. So now we have the width for each of these items, how big it's supposed to be. Then we're going to say push item width and then width each. Then we will say ImGui.push style color. Well, we'll wait on the style colors in just a minute. First of all, we'll just say if ImGui.button X. So we're just going to make this an X button. And then we're going to say button size.x, button size.y. So if this is pressed, and then we'll say values.x equals reset value. So basically, if you click this button, it resets the value. Let's see what this looks like. So if we click onto this, then we click transform. There we go. We've got an X button. If we click that, it resets its value to 0. So now we want the little drag control thing where you can drag a float. So we will do that now. We'll say ImGui.SameLine because we want this all to be on the same line. Then we have to say float vec values x equals values.x. And we'll say ImGui.dragFloat. So we'll just do a drag float and hashtag x. Make sure that we don't get a label, but we do get a unique identifier. And then we'll just say vec values x and 0.1 for the speed. You could change that if you want. Then we'll say ImGui.pop item width and ImGui.SameLine so that we can place the next thing on the same line too. I'm going to comment this out real quick so that we can see what this looks like. Now if we go into here and we click transform, we have this drag float, which would be modifying the position, but it's not right now. We'll fix that in a minute. Okay, now we want the Y control. So the Y control is basically going to be the same thing, except we just want it to say Y. So we'll copy all that. Then we'll change this to Y. We will change this. That should be fine. We will change this to Y. And then we will change this to vec values Y and change this to Y. And change this to vec values Y. Okay, and change this to Y. Okay, so that should be it. Then at the end of the function, we just want to make sure that we actually set the values to whatever they changed it to. So down here, I'm just going to say values.x equals vec values x 0, values.y equals vec values y 0. Okay, so now we should have both of these controls and they should work fine. So if I click onto here, we've got this and we can move it, and we've got this and we can move it. And if we hit Y, it resets it to 0, resets it to 0. Cool. Now let's just give these a color. We just want to color this button red and color this button blue. And that is simple enough too. So if we go to right before we actually do the button, which is right here, we just want to make sure that we push some style colors. In ImGui, the way you do that is you just say push style color. And we're going to do ImGui color.button. And then we just do RGBA. So if you hit Control P, just RGBA. So I'm going to do 0.2, 0.7, and 0.2. And these are, once again, the Cherno picked these colors. I did not pick these colors. So you can set them to whatever you want if you want them to be something different. Then I'm going to say this is button hovered, and I'm going to say this is button active. And for button hovered, we will just make this 0.3, 0.8, and 0.3. And this is wrong. This is green. This should be red. Yeah, so disregard that. This should be red, and then the next one should be green. So actually, let's just copy this and paste it down here. And then right after we do the if statement, we'll say ImGui.pop style color 3. Then up here, we will just make sure that this is red, and we want to go ImGui.pop style color 3. So we pop the colors that we just pushed, and we will change this to be 0.8, 0.1, 0.15, and then I'm going to go ahead and just copy that, paste it over here, and then paste it over here. And then for this, we'll just go 0.9, 0.2, and change this to 0.2. Okay, so now we should get some colors to our buttons. And if we go back in, and sure enough, we get a red and a green, which is matching the gizmos. Cool. So we have gizmos and we have the positions. And now if we go ahead and go into our transform class, remove this so that it just uses the default ImGui functions. Then if we go in, we should notice that it has all of our variables exposed, except it's not using the new function we just did. So how do we make it use that function? Well, we just go into component right here. And inside of our giant ImGui catch-all function, we'll just go down to vector2f. Instead of doing this, we will say JImGui.drawVec2 control, and we'll just use whatever this is. And label is going to be position, or no, not position. Label is going to be the name. So we'll just say name, and then the value is going to be just the value. Okay. And then if we go, we should see that this is now working properly. If we click into here, cool. We've got position, we've got scale. Now we need to fix rotation and z-index, which are drag float and drag int respectively. So let's just go into our JImGui class, and then we will go ahead and just copy this function. We're definitely not going to use the whole thing for drag float and drag int. So we'll go down here, we'll copy it, and then we'll call this drag float. Then this will take in a label, and it will take in a float value. And because there's no easy way to sort of like take in a float by reference, we will just return a float as well from this. So we'll keep up to here. Then we're just going to go ahead and delete all of this, so that basically we're just left with push ID, 2 columns, and then pop style var, which we don't actually need. We just want the columns 1 and the pop ID. And then right here we'll say float, and we'll create a value array because this is the only way to pass something by reference in Java. And then we will just say imgui.drag float, and we'll say hashtag drag float, and then we'll pass in the value array, and we'll say 0.1 for the speed once again. And then down at the bottom here, we'll just say return the value array 0. That way we sort of do this whole thing by reference. And then we're just going to set this to default column width. Okay, cool. So this should work for drag float now. Let's copy this once again, make another one for drag int, which is basically the same exact thing, except we take in an integer, we return an integer, we call ImGui's drag int, and we take in an int array. There we go. So that should be it. And then if we go back into our component class and we fix up float, which is right here. So instead of doing this, we will say up here, we'll say field.set, and then we want to set this, whatever object we're currently operating on in here. And then we want to set it to JImGui.drag float, and we will just pass in the label, which is the name, and the value, which is val. Okay, copy that. We'll do the same thing for integer, so we can remove all of that. And this is a drag int, and we should be good now. So if we run this, we should see that everything looks a little bit nicer. So if we go into here, cool. So we got position, scale, rotation, z-index. This is all automatically exposed for us. And then we got this sprite render thing and this stuff. For the sprite render, I am going to change this up a little bit too, because I don't really like this giant color picker thing that we've got. So let's go into JImGui and we'll create another function. I'm just going to copy this again, and we're going to call this color picker 4. So takes in a vector 4, and then I'm just say vector 4f. And this one is actually going to return a Boolean 2, which technically with the drag vectors, it probably should return a Boolean 2. And you can add that if you want. You'll see how to once we do this. So we're basically going to say Boolean res equals false. So the result is false. And then we'll go down here and we just basically say set the column width, and then we create an ImColor. So I'm going to say float ImColor equals, and I'm actually going to do it this way, color equals, and then we'll say color.x, color.y, color.z, color.w. And then we will go into here and we'll say if ImGui.colorEdit4, we're just going to call this color picker. Then and we want to pass in the ImColor array, and then we'll say color.set ImColor 0, ImColor 1, ImColor 2, and ImColor 3. Then we'll just return, or we'll say res equals true. And then at the bottom here, we will return that result. And that should be good. So now we have a color picker that we can use. So if we go into our sprite render, you'll notice too that I was using basically the exact same thing that we have in here. So this is basically what I was referencing. And then instead of doing this, we'll just say instead of if j all this, we'll say if j ImGui dot color picker 4, and then we'll say color picker, and I actually have to fix something in there too, I notice. And then we'll say this dot color. And then we'll just set this dot is dirty to true. So you'll notice this makes our functions a lot simpler too. And then let's go back into JIMGUI because I did mess this up. This should not say color picker, this should say label. So we give it label and then we do all that stuff. And actually I'm not even gonna do that. I'm gonna say hashtag color picker because we have the label right here. Okay, so then if we go ahead and we run this again, we should notice that everything looks a little bit nicer. So yep, we got the color picker. Transform looks good too. Now, if we go into level editor stuff, you'll notice that it has all the different things we have in here, which is really cool. But you'll also notice, if I can find one, I can't find one, but clearly we need to fix up some other things like booleans. This doesn't really look right. Oh, that's really cool too. But basically, we need to fix up the styling on a few of these other things, but it's very much the same as what we just did. So I'm going to push the code. You can take a look at the code if you want, but it's basically going to be the same exact thing. One other thing I do think we should fix is this scaling. So if we do scale, it resets it to 0. That's not good. That should reset it to 32. Ideally 1, but we'll talk about that at a later date too. So to fix that, we can really just fix that really easy by going to transform. And then we'll override ImGui and then do this ourselves. So we'll just say public override public void ImGui. And then we'll just say j ImGui dot drawvec2 control. We want to say transform, or actually position. This is this dot position. And we'll say j ImGui dot drawvec2 control. This is going to be scale. This dot scale. And then we'll say reset value is 32. So it resets it to 32 instead. Then we want to do a drag float for our rotation. We'll say this dot rotation, and then we'll say j ImGui dot drag int for our z index, and we'll just say z index here, this dot z index. Okay, so if we do it manually, that should fix that up. And then if we go ahead and click onto this again, if we change the scale, then we hit the reset button, it resets it to a nice even number that we would expect. We'll fix this type of stuff up to later because I don't think it should reset to 32. And we'll talk about that stuff in a little bit in the future. But yeah, so that is it for the properties panel. We now have a properties panel that is working a lot better. And you'll notice that it automatically exposes everything. Like these things, we never wrote any code for this. It just figured out how to do this because of some stuff we've had in place earlier, which is really cool. I'll push the code up. You guys check it out and see how it works so that you can implement the rest of the styles. In the next episode, we're either going to be working on like a tree, a scene hierarchy tree, so that we can click on objects over here too and do that type of stuff. Or we'll be working on getting this scale so that 1 makes it look like it's 32 and the camera's just basically zoomed in way further. We'll talk about that in the next episode. So we'll see which one we do.
In this episode, we are going to begin integrating Box2D, a Java port, into our game engine. So you can see over here, I've got a rigid body and a Box2D collider, and these are basically going to be this collider, and then it's going to have a rigid body attached to it. And in the next episode, we'll have a play button up here that we can click play, and then we will be able to use Box2D to start simulating the physics in our game world. And we'll also be adding in this thing where we can basically just right click to add in a new collider, and then we can also add in a circle collider, and you can see that all the context pops up right here. Okay, so I don't know how far we are actually going to get with all this. I don't know if we're going to get to this point because everything does take a little bit, but we'll get started and then we'll finish this up hopefully in the next episode. So first we need to integrate Box2D. Well, how do we do that? The library that we're going to be using is this JBox2D that I found, and so we can click onto its GitHub, which is right here. Tulsidas is the guy that looks like is merging pull requests, so I believe he's the author, and it's basically just jbox2d/jbox2d. And if we scroll down here, we can see that he says check out the wiki for some help. And so if we check out the wiki and look at the quick start, he basically says that he does not have anything for Gradle, which is our package that we're using. He does have Maven, but not Gradle. And so he says that you can just place the jar in your project. Well, he's a little misleading here because it's not quite that easy. If we click onto code and then this 16 tags thing here, which is the way you can get to the releases now from GitHub. I don't like this new method, but this is how you get to the releases that I know of. You can go over to here and then we can go ahead. I'm going to do 2.2.1 because this says beta and it hasn't been updated in 6 years. So we're going to go with 2.2.1 and hopefully that is stable. From what I've seen, it does look pretty stable. And we're going to click the zip and download this. I'll also have a link directly to this in the description. Download this into your downloads or wherever you want to download it to. And then just hit show in folder. That will pop this guy up and then you can go ahead. I'm just going to rename this YouTube JBox2D so that I can show you how to do this. We'll hit extract all and then just extract all of that. If you don't have 7-zip, by the way, too, just download 7-zip or any other sort of zip manager. And then we can go ahead and click into here, and this is where all the source is going to be. It's just the code, which is kind of annoying. It's not actually the jars. So let's take a look at how to import this into IntelliJ and then extract the jars. Okay, so next thing you're going to do is just open up IntelliJ, and then you're going to go up here and hit File, New Project from Existing Sources. Navigate to wherever you download that. Just paste in the path here. Mine was in YouTube JBox2D. And then click on the folder inside of that extracted folder, which in this case is jbox2d-jbox2d-2.2.1.1. Hit OK, and also notice there's some Eclipse files in there. And then we're going to hit import project from external model, which in our case is Eclipse. So just click Eclipse and then hit next. All right. Then we want to say create the module near the .class path files. That's fine, and then we're just gonna hit next. So just leave all that default, and then this is fine too. Just leave all that, and then hit next. Hit next again. Everything is fine. Hit finish with 1.8 as your source. If you want to use something else, you can. It's gonna give you that warning. That's fine. Just hit OK, and then it should open up into a new project. Okay, so now that we have this project open, we're gonna be working over here to get this to work. So in order to get this to work, we sort of have to jumpstart this a little bit. If you right click on jbox2d testbed.jogl, J-O-G-L, and then if you hit the build, it's gonna say cannot start the compiler, the SDK is not specified. So we'll hit OK there. Then it's going to say that it's trying to use Java Standard Edition 1.6, which is not what I want to use. I want to use 1.8. So just switch that and then click up here, switch this to 1.8 or whatever version you're using, and then do that for all of these. And once you go through and fix all that, you can go down, and this button right here is the OK button. It's kind of small on my screen, but if I hit that, then that should switch all of those. And then we're going to right click here again, and then we're going to hit build. Okay, and so then you'll notice that we get a bunch of errors because it's saying all these things don't exist. Okay, and so to fix that, if you just go ahead and right-click this pom.xml file inside of the directory here, if you right-click that and then if you hit add as Maven file, it will show that down here. I clicked it already, so now I just see add as amp build file, but if you click that, then that should fix up all the errors and it should build when you go ahead and you click build module. And then everything should go fine. Then if you just click into source main Java, this is just to make sure that whatever you have is working correctly. Right click on this main and then hit run testbed.main. And if you run this, you should get something that looks like this. And you can sort of go through, it has some help here, and then you can go through and test a bunch of different things. So like if you hit the right brackets 2, I believe, it switches tests. So you'll see that these are some dominoes. Go through this. This is all the things that we will be able to add to our engine, the functionality. And it looks kind of weird, but that's because he's using Java's built-in GUI. But ours will look like our engine, and we'll just be able to use this physics, okay? So if that all worked, then that means that this is working for you, so you should be good. Now we'll go up to here and then right-click JBox2D library and hit build. Just make sure that this builds. You'll see it's doing some stuff up here. Okay, so it's not building. And for some reason, I realized this when I was doing it. He has a duplicate package in here. I'm not quite sure what the reason for that was, but I just deleted this GWTE mul. So I just deleted that. And if you build it now, it should build fine. So if we just run this one more time, build, then you should notice it's almost working. And then if you right click on the pom.xml, we have to add this as a Maven project, and then that should resolve all the dependencies. Now if we hit build, it should finally build this. Okay, so now it is building, and that all worked. Okay, good. So now that you can build this, we need to make sure that this outputs a jar so that we can use it. So in order to do that, we need to go ahead and hit Control-Alt-Shift-S, and that will open up this library. This is the project structure. Okay, go to artifacts. This is where you can basically say, hey, I want you to output a jar. We'll hit plus to add a new jar, and then I'm gonna actually do this from modules with dependencies, and then I'm gonna go ahead and click on jbox2d-library because that's the one we want to create a jar from. We don't have a main class because this is just a library, so just leave that as is, then we'll hit OK. That should do everything for us. Hit apply, hit OK. So to build the artifact now, what we have to do is you have to go up here, click build, and then hit build artifacts, and we want to make sure to build jbox2d library jar. So just double click that, and that should begin the build process, and I believe it finished. The way to check is just to go into the folder, and you should have an out directory now. Click into that, click artifacts, and then just keep clicking, and you'll run into this jbox2d library jar. Okay, so now we have the jar. Now we want to make sure to add that to our project. So go to your project for our game engine, which in my case is in C Dev Java Mario Dev branch. Okay, go into there and then go ahead. Actually, mine is inside of Mario YouTube. And then we're going to go ahead and create a new folder, Control-Shift-N, call this libs, and then we're just going to move this jar into the libs folder. Okay? Now we have the jar. So I'm going to exit out of this, and I'm going to exit out of this by opening up our project, which is this Mario YouTube. So I'm going to just hit open this into this window. And now if you remember where we left off, I believe, yeah, we just left off with like these things, and we can sort of pick colors and all that stuff. So that's all good. Now we want to import this file into our Gradle project, right? And so the way we do that is if we go into our build.gradle file, which is at the bottom here, we're going to have to basically tell it, hey, we have a jar that we are adding manually to the Gradle. And so the way we do this is we first say, hey, there's a flat directory, which just basically means there's a directory on my machine, and the directory's name is libs. Okay, so that corresponds to the libs folder we just created, right? So we're just telling it, hey, there's a directory called libs, and then inside of that directory called libs, we have this jar called jbox2d-library.jar, right? And so we can tell it that we have that, and I'm going to go down here and just say box2d, and we can tell it we have that by just saying implementation name and then jbox2d-library. And then if you hit import changes down here, we should be able to import those, and I believe that was fine. Let's open up that window just to make sure. Okay, yeah, so if you open up the build window and it says configure successful, you're good. That all worked. Okay, so now we have the implementation in there and we have access to this file. Now we have to actually start adding all of the stuff that we're going to need. So first of all, what I'm going to do, I'm going to go ahead and just collapse this and this and this and this. So if you're following the Physics 2D series, you'll know that I have this package called Physics 2D. I'm going to go ahead and just refactor this and rename it to Physics 2D temp. And I'm just going to hit refactor. That should rename everything. Then I'm going to go into here and create another package, call this Physics 2D. So Physics 2D temp is temporary because I'm only using that to teach you guys how to build a physics engine. It's not meant to be a final physics engine. This is going to be the wrapper around the actual library that we just imported the jar for, okay? This Physics 2D package. So now we're going to go into this Physics 2D package and we're going to create a new class, call that Physics 2D. This is basically going to be our wrapper around everything, sort of like our renderer class inside of our renderer. So inside of this physics 2D package, we're going to need a couple different things. We're going to need an update method. So we'll take in a float delta time. Then we are also going to need a few variables that we will use to update our physics engine. So we will do private vec2, and the reason we're doing this vec2 is because we're using it from JBox 2D. So this is their math type, and we're going to say this is gravity equals a new vec2, 0, negative 10. Okay, so you can figure out sort of what types they use by just typing in the names that you expect their types to be. And the way I know what I'm doing right now too, by the way, is by going to Box2D's actual website. So if we look at Box2D and we zoom this in a little bit, then we can go to documentation. And then if you look at Hello Box2D and creating a world, we'll just jump into here and see what happens. Okay, yeah, so if you go into here, then there's a bunch of these things. So we have this bvec2, this b2 world. I'm literally just following this tutorial, okay? So he gives you a tutorial on how to use Box2D, and it's very similar in the Java port that we have, except just minus the b2 in the front of all of these types, okay? So this is how I'm figuring out what I'm about to do here. So we're going to need a private world, okay? And that equals a new world, and we're going to use gravity, right? So this world just uses this gravity. And then I'm going to have a variable that we're going to use, public float physics time, and this is just so that we can keep our physics time going in a continuous concrete interval, right? We want it to go at 60 frames per second. And I'm going to create another thing here, call this private float physics time step equals 1 over 60, so 1.0 over 60. And that's just 1/60th of a second. We want it to go 60 frames per second, our physics, okay? I'm just going to go ahead and indent that one more and then say private int, and this is going to be our physics. Well, we'll just call this velocity iterations, and I think I set this to 8, and then private int position iterations, and this is set to 3. And the reason we have to set these is because Box2D uses this thing called a iterative impulse resolver. So it uses a certain amount of iterations for the position and the velocity to resolve those whenever collisions happen. And we have to provide how many iterations. The more you have, the better your physics will be, but the slower it will run. So this is a good happy medium. I think I pulled this from their website. I'm not sure where I got these numbers from. Pulling this from my actual game engine, which is where I got it. Okay. Then what we're going to do is we're going to say physics time plus equals dt. If physics time is greater than or equal to 0, then we're going to say physics time minus equals physics time step, and then we're going to say world.step physics time step, and then if we control P, we can see we need velocity iterations and position iterations. Okay, so what am I doing here? Well, basically what we want to happen is we want to make sure we update our physics only once every 60 frames, right? But our game engine could technically run 0.16 milliseconds frame 1, and I guess that's seconds. So it could run 16 milliseconds frame 1, it could run 17 milliseconds frame 2, it could run 20 milliseconds frame 3, and then go 14 milliseconds frame 4. It's not going to be stable, okay? And so what we do to combat that is we basically keep track of where we're at. So we'll say we'll start off at 0, then we'll add in whatever delta time for this time step was. So say that was 16 milliseconds. Now all of a sudden we're at 16 milliseconds, so we have to make sure we subtract that. So then we'll say 16 milliseconds minus 16 milliseconds. And we're subtracting this because we have gone inside this loop because we were greater than or equal to 0. So then we step the world by 16 milliseconds because we have indeed gone that much. Then let's say next frame is 14 milliseconds. Well, then we go 14 minus 16, which equals -2. So now we're at -2. So then the next frame, we won't update the physics because we haven't actually gone through 16 milliseconds yet. So then next frame, let's say, is 16 milliseconds. Then it would be -2 plus 16, which equals 14. And then we would get enough for an update. So then we would update, and then we would say, okay, 14 minus 16, and that is -2. And then basically the process repeats. So we're just sort of incrementing only once we've passed 16 milliseconds is all this is doing. So we may skip a frame or two, when we're updating the physics, and that's perfectly fine because that may be needed. Okay, let's go ahead and add the components that we're going to need. I'm going to go into here and create a new package and call this components. And I'm going to create another new package and call this enums. So we're going to need one enum, and we're going to create a new Java class, call that body type. This is basically just going to be the body types that we could have, which are static, dynamic, and kinematic. Okay, and these are just straight from Box2D. We're just creating our own types so that users of our engine can use these types, okay? Then we're going to go into components, create a new class. We'll call this rigid body 2D. I'm going to hit add that to Git. And this class will take a private vector 2f, velocity equals a new vector 2f. It will have a angular damping, which I will initialize to 0.8, and we can tweak all these initial values in the future once we can actually start using this. We'll say linear damping equals 0.9f, we'll say private float mass equals 0, private body type equals, import that from where we just created that class, physics2d.enums, and then we'll say body type equals body type.dynamic, and then we'll say private boolean fixed rotation equals false private boolean continuous collision equals false, and then, or actually true, and then we'll say private body raw body equals null. Okay, these are just sort of all the variables that we're going to need to wrap around JBox2D. So they need the velocity, angular damping, linear damping, mass, body type, fixed rotation, and continuous collision. These are all the settings that we'll be able to set, right? And we'll want to be able to set those inside of our components. I'm also going to go ahead and create getters and setters for all these. So if we go to code and then generate, we're going to say getter and setter, and then we just want to create one for every single variable. So do that. That should be good. And then we're going to go ahead and say that this extends component because we will want to use this as a actual component. And we'll also go ahead and override public void update float delta time, and this update method will say if raw body does not equal null. So if we have added this to box2D and we're updating this, then we'll say this dot game object dot transform dot position dot set, and then we need to say raw body dot get position dot x and raw body dot get position dot y. And I will explain why we're doing this in just a second. We will also need to do this dot game object transform rotation equals raw body dot get angle, and we'll want to convert this to degrees. So we'll say math.2 degrees, and then just wrap that in that call and cast it to a float. All right, so why do we do this in the update method? Well, basically, since we're wrapping around a library, that library uses its own types. So we basically have to create its type, which we're calling the raw body. We pass that to the game engine, or to the physics engine. Physics engine uses this, optimizes it, does whatever it does with it. Then inside of here, every frame, we make sure that we're matching what the physics engine says. So if the physics engine changed the transform in the last frame, then we match the frame, the position, to whatever his position is. Okay, so that's why we have that. Let's go ahead and just create a new class, call this box2D collider. We'll hit add and then create another new class, call this circle collider, hit add, and then we'll just say this extends component, and we can just import that and then do the same thing here, extends component. All right, import that as well. Okay, then we'll just go into here, say private float radius equals 1 by default, alt enter, create getter and setter. All right, so that's getter setter, and then inside here, once again, we'll say public or private vector 2 half size, and then we'll say create getter setter. That should be good, and we'll initialize this to new vector 2f1. Okay, so this is sort of the basis of everything that we're going to need. We're running a little bit long here, and that's because there's just a lot of stuff that we have to do. So in the next episode, we're going to continue to work on this and hopefully get the rest of our stuff running so that we will have what I showed you in the beginning of this, which is the ability to click onto here and we can sort of edit these things, and it edits them in the viewport, and then we can click onto one, add a rigid body, and it adds a rigid body, all that stuff. And then we'll also hopefully add in a play button here so that we can play the physics simulation and see it working. So in this episode, we're not going to be getting all of this done, but we are going to start working towards this. I went ahead and started coding quite a bit in the development branch just to show you guys what we will be working towards. So this is sort of where we're headed, and it's going to take quite a bit of changes. I have a link to the GitHub diff so that you can check that out. But basically, we'll be able to add objects, duplicate objects, and then you'll see this has physics attached and everything. We can play and stop the scene. We can delete objects, and then if I go into here, I can change some of the physics things. So like if I change this to a static object, it won't move, but it still has physics applied, so it just gets stuck there. And then as you can see, we have physics like completely working, and we can play and stop our level just by doing this, which is really cool. And it's just a lot of cool stuff that we will be getting to. So if you want to see all the changes I had to make to get here, check out the description for a link to the GitHub diff, which looks like this. There's quite a bit of changes in here because I did a lot of refactoring and stuff too, so that we can get to a better point with the code base and hopefully have it working a little bit better. But you can check this out, and then if you want to work ahead. In this tutorial, what we're specifically going to be doing is we're probably going to be adding the functionality so that we can actually create a physics object, and then so that we can right click in this properties window and then hit like add rigid body or something. So if I were to place in a new object in here, it doesn't have a rigid body, but if I right click over here, I can say, hey, add a box collider, and then that adds a box collider, as you can see, and then I can say add a rigid body. One other thing that we'll be doing, which is kind of cool, is like if I toggle the physics debug drawings, so it's kind of glitching out here a little bit, but this is basically Box 2D's physics debug. So like I had to enable Box 2D's physics debugging drawing because I couldn't really tell what was wrong with mine, and so I did all that, and then I'll probably just be giving you guys the code to that so that you can use it whenever we get to a point where this will be necessary. But yeah, so you can see that this all works just like you would expect it. Okay, so let's get started, right? Very quickly, before we jump in and start coding, I do want to mention, because we will be building this event system. Remember I had talked about how I wanted an event system and it will just make some things nicer. I can't remember what I specifically wanted it for, but we're going to be doing that in this episode as well. This shouldn't take too long because setting it up is actually pretty simple. So the premise of an event system is basically, and we're following the observer pattern here too, which I'll have a link to the description to a article on this. But basically, we want a bunch of observers that say, hey, every time there's an event, and maybe when there's a specific event, I want to be notified of this. We don't have the specific events for this episode. We're just be doing like generic, hey, whenever something happens, I want to know about it. And then we have some event system that basically says, okay, I'll go ahead and notify you of those events. And this is literally all there is to it. So event system will literally just look like a class that has a list of observers, right? And so whenever we call this on notify message to the event system, so like maybe we want to notify of something, then we just go ahead and loop through all the observers and call their abstract on notify message. The thing that makes this so powerful is that our on notify will basically have two parameters, one which is a game object, which I'll preface with GO, and the second which is an event. And the event can hold data, and it can also hold just a simple event type. The reason this is so simple or so powerful is because now all of a sudden we have a way to go and reach out to hundreds of other systems potentially that wouldn't be very performant and just notify them with a specific game object or nothing if we don't want to. We can just leave that null and then event, and they'll be notified and we don't have to couple them. This is completely decoupling. So we do have this global event system now, and we do have to manage these observers, but it's a pretty good pattern. This isn't very performant too, so we're only going to be using it for tasks like on, begin, play, and stuff like that, right? So we'll have a bunch of different event types that we can just call, which are very simple, and that will make sure that we're not using this like inside of a core game loop or something, because then it will become not so performant. We could improve it in the future if we want to as well. Okay, so this is the basic premise of the whole system. Let's go ahead and code this because I think it's pretty cool, and it'll definitely help clean up our code a little bit in some areas. All right, so let's very quickly code up that event system or observer system that I just talked about. It really is as simple as I just talked about too. There's nothing too complicated. So let's just go into our Java and we're going to create a new package and I'm going to call this observers. All right, and so this will sort of contain the code that relates to this whole observer system. Then we'll go into here and we'll create another new class, call this event system. And so this will sort of be our global event system that handles all the observers. We'll create another class, call this observer, and this will be an abstract class that has that onNotify method. And then we'll create a package, and we're going to call this events, and just create everything up front. And then inside of here, we'll create a new class, call this event type, and this is actually going to be an enum, so click that enum. We'll have that, and then we're going to go ahead and create another new class inside of here. Call this event, and this is just going to be empty for use to be extended if we want to send a specific event in the future. Okay, so let's go to the observer because this is sort of where all the magic happens. And it's literally just a simple, we're going to call this an interface so that other classes can implement it. And it literally just says onNotify, and it takes in a game object, and it takes in an event. And we'll hit Alt-Enter, import that. And I imported that from the wrong, wait, no, I did. Okay, make sure you import it from the right package. This is literally all that's inside of Observer. It's just an interface that says, hey, onNotify, and then we send it a couple things. And now we can implement this in any class, and then they will be notified whenever an event happens. For the event system, we're going to keep it just as simple. We'll go into here and we'll just say private static list of observers. So we're going to hold the list of observers and we'll call this observers equals a new array list. Then down here, we're going to say public static void add observer, which will take in an observer. And we'll just add it to our list of observers. So we'll say observers dot add observer. And then we'll have one more function called public static notify. And this will just take in a game object, obj, and an event. And I will import that using Alt-Enter. And also this function should return void. Okay, and then this will literally just say for observer, observer in observers, observer.notify.onNotify, and then I'll pass in the object and the event. That's all we need. This will now work with our game engine and allow us to notify things in completely different classes of events going on throughout our system. Now, unfortunately, I don't think we're going to have time to actually use this today, but we will be using this like in the next episode or something whenever we go to implement our physics. And the way it's going to be used to is an event actually will have an event type, and we'll just call this event, or we'll just call this type. And then this will be public, and it will just sort of tell us what type of event we're using. And we'll create a couple. We'll say game engine start play, game engine stop play, and then we'll have one for save level and one for load level, and then user event. The user event is sort of just a catch-all to say, hey, if in the future one of the users wants to extend this and create their own event or whatever, they can just use it and then say they have a user event and then do what they want with it, and we'll just ignore it because it's a user event. It's not one of our built-in events. Okay, and so this you can sort of probably see how we'll be using it in the future as well. When we get a game engine start play, we can start the physics, and then when it stops, we can reload back to where we were before we started the physics and everything. But we'll see how to use all this in the next video. I just wanted to put it in place so that we have it. Okay, let's go back into our physics 2D now, and we're going to need another function in here, which I am going to call public void add, and this will take in a game object, go, and this is literally just going to add it to the physics engine. Okay, so we're going to add it to box 2D throughout here. Now, what I'm going to be doing is basically taken directly from his tutorial that I showed you in the last one, which is basically just the hello box 2D, and that's where I'm getting all of this information from, that in his documentation. So let's first of all say rigid body 2D rb equals go.getComponent rigid body 2D.class. So if a game object has a rigid body, then we will add it. So we'll say if rb does not equal null. So if they do have a rigid body and rb.getRawBody does equal null, the rb.getRawBody basically tells us, hey, this has not been added to the physics engine. This has not been added to Box2D yet. But if this is null, if this is not null, then that means that it has been added Box2D, and we don't want to add it a second time. So this is just like sort of a safety in case somebody tries to add the same game object twice to the physics engine. Okay. Then we're going to get a hold of the transform. We'll just say transform equals go.getComponent. Actually, we can just say go.transform. Okay, that's nice and easy. This is where the Box2D code starts coming in. So we'll say body def, which is the body definition, equals a new body def. And this is how we will tell it how to create the body. So first of all, we're going to say body def.angle equals, and then we're going to go ahead and say float math.2radians transform.rotation. Then we're going to say body def.set or .position.set, and we're going to give it the transforms position.x and the transforms position.y. And we're just going to set the rest of these settings directly from whatever the user provided. So we'll say the angular damping equals the rigid body's angular damping. We'll set the linear damping to the RB's linear damping. We'll set fixed rotation to the RB.is fixed rotation. And then we'll set the body's bullet to RB.is continuous. So bullet is basically what it's called whenever you have a continuous collision, and this just means that there won't be any ghosting of objects. Now, if you don't know what that means, I suggest you Google it, but basically it just means that if you have a bullet, it's called bullet because this is usually where it occurs, but if you have something traveling like as fast as a bullet, and say you have a wall here, sometimes what happens is the bullet is right here, one frame, then the next frame it's over here, and it just clips through the wall. So when you turn this bullet on, it basically just says we're going to use continuous collision, and so then it makes sure that the bullet actually hits the wall instead of just going right through it. That's all that is. Okay, then we're going to say switch rb.getBodyType, and we're going to say case kinematic. This is just standard physics terms. If you've used Unity, you'll probably recognize these, and we'll explore them more as we actually code them and see how they work. We'll say if the body types, so if we have a kinematic body, we just want to set the body definitions type to org.jbox2d.dynamics.bodytype.kinematic. And the reason we have to do it, okay, and I guess in my old code I had done it the whole path because I had some name collisions, but it looks like we're good in this case, hopefully. Then we'll say case static, and we'll take body type's definition to static, and then we'll break, and then we'll say case dynamic, which is probably what you'll want most of your physics types to be. That and static are actually probably what you're going to be using most of the time. And then we'll say break on that as well. Okay. So this creates the body definition, right? This creates what we're going to use to figure out how much friction, all that type of stuff. And I think I might have actually missed that as well. Oh, no, I didn't miss that. It's just linear damping. Okay. So yeah, we basically tell it this is like angular friction. This is linear friction. And then we tell it whether we want it to be fixed rotations that can't rotate or not and all that stuff. Next, what we have to do is basically tell it what the collision shape is. So we, in our game engine, we're currently supporting just circles and boxes, right? So you can have a circle or you can have a box. And we have to tell Box2D that by creating something called a polygon shape. And so the way I did this is I just say polygon shape equals a new polygon shape. And then we can set this as either a circle or a box, which is good for us because we don't really know. And then what I'm going to do is I'm going to say circle collider because we don't know if we have a circle collider or a box collider at this moment is null. We'll actually just set it like that. And then we'll say Box2D collider. Box collider is what I'll call that. And then we can say if circle collider equals go.getComponent circle collider dot class does not equal null. So you may not have seen this syntax. It's probably more common like C++ and stuff, but basically all this does is it assigns this go.getComponent to circle collider, and then it checks and sees if that was null or not. And we just have to declare them beforehand in order to do this. And the only reason I'm doing it this way is because then we're going to say else if box collider, and we're going to do the same sort of thing, equals go.getComponent, box collider dot class does not equal null. And it literally, it's probably not even worth it. It saves just one function call to this, which we know is just a linear search. So theoretically, it probably saves a tiny little bit of performance, but it's really not necessary. So if you don't like this syntax, just assign these up here and then just check and see if they're null down here, which is all we're really doing. So if it's a circle collider, what we say is shape.setRadius. And I'm not actually sure if this is going to be correct yet, but we will find out in the future. Circle collider. And what I mean by that too is just if it's like in the correct position and stuff. I haven't tested this one yet, but the box one I know for sure. And then we'll just get the radius. So this will just set the radius to whatever our circle is. And this also implicitly sets this polygon shape to a circle. And we'll say bodydef.position.set transform.position. And actually, I'm not even going to do this part because we don't know for sure if that's going to work yet. We'll settle that in the future. Okay. Then if we have a box collider, we'll say vector2 half size equals, we're going to say new vector2f box 2D collider or box collider dot get half size dot multiply by 0.5f. And you may be asking why I'm multiplying the half size by half. And that's because when I was testing this, for some reason I had to multiply it by half again in order to get it the correct size in box 2D as it was. So like all these numbers and stuff are just so that I could get box 2D to match what is actually showing in the engine. And we'll talk about that a little bit more once we get some debug drawing up and you can actually see what that means. And then we'll say vector2f offset equals box 2D collider or box collider dot get offset, which we don't have yet. We'll add that in a minute. And then we'll also say vector2f origin equals new vector2f box collider dot get origin. And we will also add that. So if we go into components, I'm going to go ahead and create a new class. We'll just call this collider. And then inside of this collider class, which we're going to say extends component from our components class. And then we're also going to make this abstract. This is going to have a public or private vector2f. And this is going to be our offset equals new vector2f. And so this is basically like sometimes when you import assets, you need to move the colliders around a little bit to get them to fit correctly on the asset. And this is what this will be used to. We'll just have a public vector2f get offset. And this will return this dot offset. All right. And then circle collider and box collider will both extend from collider instead of that. So we'll just have this extend collider. And we'll have this extend collider. Okay. And then we're going to go ahead and also add in an origin. Vector2f origin equals new vector2f. This will probably remain 0, 0 like for most of the time, but I figured we could have it there just to mess around with it in the future if we want and see how that works. And then we'll have a vector2f get origin, which returns this dot origin. Okay. Now we can go back into our physics 2D class. So we have all these values now. And we want to pass them to box 2D so that we can set this all correctly. So we'll say shape.set as box, half size.x, half size.y. And then we'll say new vec2 origin.x and origin.y. And then the angle, which we'll say is 0 for now. We may change this in the future too. Who knows? And all this basically does is it just sets this polygon shape to the shape of our box. It's literally all it's doing. And then we'll say vec2 pose equals bodydef.position. And we want to basically move box 2D's box to fit perfectly over our box. And the way we do this is we say float x pose equals pose.x plus offset.x and float y pose equals pose.y plus offset.y. So we're basically telling box 2D, hey, we're going to sort of change it so that it takes into account the offset, and then we'll mirror this inside of our rigid body. And then we'll say body definition.position.set x pose and y pose. And a lot of this may not make sense right now. Don't worry, it will once we actually start messing with this stuff in the editor. We're basically just doing all the settings and then sending it to box 2D so that it can use them. Then we're going to say body equals, and I'm going to hit Alt Enter and import that. this.world.create body, and then we're going to pass in the body definition. So now we've just added this to Box2D's engine, and then we're going to say rigidbody.set raw body to this. Now we have a copy of that, and then we're going to say body.create fixture. We're going to pass it our polygon shape, and we're going to pass it our mass. All right, and then that should create the rigid body inside of Box2D, and then it should also assign this create fixture basically says, hey, create the polygon shape and actually attach it to this rigid body. Okay, so now that we have a way to actually add game objects with rigid bodies and stuff, we need a way to add the rigid body to our game objects. So how do we do that? Well, we can go into our editor and we'll go into our properties window. Remember how I was right clicking on that and we sort of were able to add things? This is where we will add all that code. And so we'll say if the game object is not null, then right before we actually ImGui everything, we'll say if ImGui dot begin pop-up context window, and I'm going to call this component adder. This part will not be seen by any of us. This is just the ID, so this is just used internally. Make sure it's unique. And then we'll say if ImGui.menu item, and then I'm going to say add rigid body. So if they click add rigid body, we're going to say if active game object.get component rigid body.class equals null. So if they don't already have one, then we'll add it. We'll say active game object.add component new rigid body. And you know, maybe in the future you will want to have multiple components of the same type added. So we'll think about maybe not having this in the future, but for now we'll just say if they don't already have it, then we'll add it so that they can only have one at a time. And then right down here we'll say if ImGui.menu item, following that exact same pattern, add box collider. So if they click add box collider, then we're going to copy this and then say add a new box 2D collider, and then we'll add a new box 2D collider. Copy this one more time. We'll do the same thing for circle collider. So we'll say add a circle collider, and then we can say if they don't already have a circle class, then we'll add it down here. Hit Alt Enter, and I'm gonna, whoops, that imported it from the wrong library. So I'm just gonna remove that, import this from the correct, which is circle collider. That's why it wasn't finding it. Okay, so just make sure you have the right names and you should be good. All right, so now we can add circle colliders and everything, and then make sure at the end of this you do imgui.end pop-up. All right, so what did that do? This basically makes it so that we can now go into here, and then when we click on an object, you can right click inside of this window, just that window. It opens this up. We have these three options. If we hit add rigid body, then it adds one. If we hit it again, it doesn't add a new one. And then you see we have everything here just like we would want it. Now, one last thing, we don't want, well, maybe in the future we will, but for now, we don't want to add box colliders and circle colliders. So we just want to say if they don't have a box collider and they don't have a circle collider, then we'll add a box component. So we'll say circle collider.class, and then I'll just copy that, equals null as well. And then we'll go down here and we'll do the same thing. So if they're trying to add a circle collider, we just want to make sure that they don't have a box collider, because then that'd be kind of weird with the way we have things right now. All right, so that should literally just do the same thing, but basically now if we click onto this and if I hit add box collider and then try to add a circle collider, it won't let me, and it won't let me add any of those as well. All right, so we have this, and now we basically want that play stop button thing that I had up here. Well, that's actually going to require quite a bit of refactoring, and I want to keep these episodes pretty self-contained. So I think this is going to be it for this episode. In the next episode, we will begin refactoring a lot, start using that event system that I talked about, and add in this play stop button up here so that we can actually play our physics simulation. In this episode, we're going to continue our integration and hopefully get it all done in this episode. It might be a little bit longer, but that's okay because I want to get the physics to the point that I had showed you earlier. So before we start this episode, I do want to go over a few things just to clarify exactly why we make some of the decisions we will. So in the last video, I feel like I was doing some code and I wasn't really explaining why the code was necessary or why it was important, and I want to do a little bit of a better job at prefacing that right now. Hey guys, this is Gabe from the future. I forgot to mention that we have a Discord. So if I open this up, then you will see that we have this whole Discord. Go and join it. Links in the description, and I hope to see you guys in here. All right, on with the video. Okay, so a game engine consists of many different parts, right? We have the highest level, which is the engine, and we can just sort of think of that. And then this communicates with like AI at some of the highest level, game logic or scripts. And then you have your physics system, which are sort of like the highest level things. And then you go into your lower level stuff like the input, the graphics, the audio. And then those go and interact with the operating system. And you have different levels of abstraction for each of these layers, everything. And you can go much more detailed than this, but I just wanted sort of a rough game engine-y kind of architecture to show you guys so that we can talk about how exactly we're integrating this physics. So each of these boxes is basically a component that should be able to stand alone, right? There are several physics engines that are just physics engines. They don't deal with game engines. There are several scripting systems that don't deal with game engines, right? We have lots of artificial intelligence engines and models, think machine learning and TensorFlow, that doesn't deal with games, right? So each of these can be like little boxes that you could technically import from a third party, and you don't necessarily need to code it yourself. Well, that's what we're doing with the physics, right? We're importing that from Box2D because it just makes our lives a little bit easier. So what that means is that our game engine is communicating with our physics interface, which is actually delegating to our third-party physics engine, which is just Box2D. And this means that we sort of have to figure out, okay, well, how do we communicate the data to the third-party engine and go back and forth between these two? And the way we do that is or the way I chose to do that is just to make a copy of the data, right? So what I said is, okay, so what does a typical physics body consist of? Well, a circle might be its shape, and that has maybe some joints, and it has a collider, which is this circle collider. And then maybe it has a mass and it has some velocity, and maybe you want to add forces to it and all these different things. Well, we can sort of abstract this into something called a rigid body, right? And we can call this a rigid body, which Box2D also does. And then we can provide our users of our engine with our version of this rigid body, copy all that data, send it to Box2D, which is this box right here, and then let Box2D do what it will with this data. Well, the problem is Box2D will be calculating every time we tell it to calculate, right? And then it calculates new positions for like, where is this in the world and all that stuff. And it just figures all that stuff out. And unfortunately, that data since it's a copy of the data that we're sending over there, we're not getting notified of these changes. So what we have to do every frame is come up with a way to say, hey, Box2D, we need to sync with you. And so this is sort of like our sync step. So we say, hey, and sync does not have an E at the end of it. That is spelled wrong. So we have to say, hey, Box2D, tell me what the position of my transform is and all that stuff. And that's sort of why we hang on to that raw object, which I think you guys will remember from the rigid body. It has this thing called a raw object, which is basically the pointer or the reference to the object inside of here. And so once we have that reference every frame, we can say, okay, let's see how this has changed. Then let's update our version of it to basically match that. And then once we update our version of it, that will make sure that once it goes through to the graphics and everything and continues down the pipeline of our game engine, it will sync the physics correctly. Now, the only problem with this is our physics API is very limited right now. Box2D has a ton of stuff that you can do. So the challenge for us is basically coming up with an API inside of our physics library that wraps around all the functionality in Box2D, and then basically just coordinates and calls to Box2D and then coordinates back and forth between each other. And I would say this is not necessarily necessary in all cases. ImGui, we have a lot of ImGui code scattered around, which we're just sort of using where we please, and we're not necessarily wrapping it all around inside of our own library, but I think this is important to wrap in our own API. That way, users of the engine won't accidentally use some functionality in here that isn't really technically supported by the engine and then might have problems further down the line. So one of the other problems that comes with syncing between these two things is if we tell Box2D that a box has like a position here, it might not sync up correctly with the way we are drawing things. So I think Box2D draws things from the center. So if it has a box, it basically says, okay, the center is where I'm going to define the position as. Whereas in our engine, if we have a box, we say the center, or we say we draw it from here. And so when you define the position, or actually I think it's the bottom left corner. So when you define a position, it's this bottom left corner. What that means is that we actually, when we're doing this syncing step, we also have to make sure we take into account that, hey, we're drawing from here, whereas the position in Box2D's mind is here. That's really not a problem for us because it just means that, hey, as long as we make sure to offset all our stuff by that distance, then we'll be matching with Box2D directly. And so for that reason, Box2D has a debug drawing library, which basically allows you to draw using all of its tools, and then it just sort of uses your render to do the drawing so that you can see exactly where it's drawing everything. And then I used this, which we're not actually going to do in this tutorial, but I did use this to figure out how to offset the thing so that when we went from syncing step, that we would be matching what we saw in Box2D. And we'll talk about that a little bit more when we talk about turning on the debug drawing. Okay, anyways, that's enough of a preface. We're going to go do a whole ton of stuff to try and get to the point that I showed you in the last video. All right, so just a quick reminder, this is what we're working towards. I just want to remind you guys, this is where we should end up, hopefully by the end of this episode. Now, the first thing we're going to need is this play stop thing, right? We need a way to be able to play and stop the scene at will, and we don't have that currently. And how are we supposed to start the physics simulation if we can't even start the physics, right? So let's create a play stop button. So where do we add that? Well, if we actually look at our code right now, we know that this play stop menu button should be at the top of this game viewport, right? And we've conveniently made this game viewport or game view window down here, which has all the ImGui code necessary to do the drawing. So if we go into here and go into our ImGui window, right after we begin the viewport, we can go in here and we can say imgui.begin menu bar, and then we'll say imgui.end menu bar. Then we can go ahead and say if imgui.menu item, and I'm going to call this play, and we'll make a shortcut, say there is no shortcut, and we're going to create a couple variables. We're going to say is playing, and then not is playing. Just do that real quick. Then let's go up to here and say private boolean is playing equals false initially. And if we take a look at what this function actually does, you can see that it takes in two booleans, selected and enabled. And so basically what we're doing here is we're just making sure that when they're playing it, that this button will be deactivated so that they can't keep pressing it. And then when they stop it, the stop button will be deactivated so they can't keep pressing that either. So that's basically what those two parameters do, and we keep track of that using this is playing variable. Okay? And so basically if the user does press the play button, we'll say is playing equals true, and then we can use our observer handler and finally begin to use this. So or actually this isn't called an observer handler, we called it our event system. We'll say dot notify, and we're going to give a null game object, and then we want to give an event. So we'll say new event, and if we import event from observers.events, we need to give it a parameter so that we can tell it what kind of event we are sending. So let's go into observers, events, and then we'll go into here. And let's just create a constructor real quick. We'll say public event, event type, this dot type equals type. So very simple constructor, basically just sets whatever event it is this way, and we can actually also create another like an empty constructor. That way if you don't want to use it, you don't have to. And we'll just say this dot event or this dot type equals event type dot user. So we'll just default to a user event, and then we can also create a specific event if we want to. So then when we create this event, we want to make sure we create an event type dot game engine start play, because we are starting to play. Then we go down here and we'll just say if imgui menu item stop, which is very similar, except we will do not is playing, then is playing, so that's the opposite. In this way, they sort of toggle each other on and off by using the enabled and disabled patterns here. We'll say is playing equals false. If they hit that, then event system dot notify. null and a new event, event type dot game engine stop play, which we have right there. Cool. So this should give us a menu bar, and then if we hit Shift F10 and build this, we get a error. Let's see what this is. Oh, and it says we failed because we violated an assertion about a menu bar. We actually need to go up here and also say that we want to allow a menu bar. So we say ImGui window flags dot menu bar. Okay, there we go. And this basically just lets ImGui know that we want to attach a menu bar to this window. Okay, and then you can notice we have the play and we have stop, and they toggle on and off when we press them. Now right now it's not actually going to do anything. Let's actually register an event handler. Okay, that way we can see how to use the event system. So right now the events are getting sent out, but nobody's listening. So we will go into our window and we'll scroll to the top of this class. And we'll just say that this window right here implements the observer. So we're basically saying, hey, we want to be notified of certain events. Then we need to make sure that inside of our constructor, and we can also remove all that, and may as well call this Jade, which I can't actually use, so that's for another time, though. The name is taken, but anyways, we'll go into here and then we'll say event system dot add observer, and then we'll just pass in a reference to ourself. That way we register ourselves, and this is complaining because we do not have the onNotify method. Then inside here we can say if event dot type equals event type dot game engine start play. For now we'll just say system dot out dot print line starting play, and then we'll say else if event dot type equals event type dot game engine stop play system.out.println ending play. So then inside of there is where we will handle that code appropriately. Let's just make sure that it is working. And we have an error here because I deleted those things that we don't need any longer. So I'm actually going to delete that as well. And let's see, where else did I use this stuff? And I'm going to delete this as well. We'll just say clear color to a white color, which should be fine. Okay. Okay, yeah, and this is an exception I ran into when I was coding this the first time too. For some reason our tests are failing now. Not quite sure why that is, but I really don't care about that right now. So what we can do is we can go into run and then hit edit configurations, and we'll just turn the tests off for now. So we'll just remove the run collision test here, and then this is my OK button. I think that applied. And then if we hit Shift F10 again, there we go, we get it running. And if we hit play stop, play stop, play stop a few times, you'll notice it says starting, stopping, starting, stopping, starting, stopping. Sweet. So that's all working like you would expect it. We can now tell when the game engine starts and stops by just sending an event and letting the game engine know, and then it just figures it out through our event system. So this is the power of this event system. It's very cool. We'll have to do some tweaking to get it to work very good with game objects and stuff like that, but we'll take a look at that in the future. Okay, now for some quite big changes. So in the code changes that I've made, I've actually completely removed level editor scene and level scene and made this not abstract. The reason for doing this is just because as I've been coding this, I've realized that this doesn't really need to be abstract, and it makes more sense to have one scene class that has it loads all its stuff from a file, okay? And hopefully this will make sense more as we actually start to code this. So in order to make this change, we're going to have to do a few different things to make this work correctly. So first of all, we're going to just mark all these as private. So I'm just going to copy that and paste over the protect keyword so that that is working correctly. And then we'll go down here to where we have these abstract methods, and I'm just going to make them not abstract by actually implementing them. So we can remove this code right here, and then we can remove this code here. And then inside of here, we'll say this .render, which is all we are doing right now, I believe anyways. So then if we actually go into here, yeah, we'll notice that this is just rendering. Then we'll go up here, and inside the update loop, you'll notice that we have all of this stuff. So I believe this is all we really need. So we just need to adjust the camera's projection and then update all the game objects. So we'll go into scene. I'm actually going to delete level scene too, so we'll delete that right now. Paste that into here. This should update all the game objects, adjust the projection matrix, which is perfect. Then we're going to add something new. So let's go into here and create another class. We'll call this scene initializer. And this may get deprecated in the future too. I'm not quite sure yet. But basically, this is just going to have a couple of functions that we can use to sort of maintain this functionality that we're doing. So inside of here, we'll have a public abstract init method that takes in a scene. We'll have a public abstract void method, and these are all void. And this will be load resources, which also takes in a scene. And then we'll have a public abstract void ImGui function, which does nothing right now. Then inside of our scene, we will go ahead and say this takes in a private scene initializer, which we'll just call scene initializer. Then this will take it into the constructor so that we can set it in here. And then we'll just say this dot scene initializer equals scene initializer. Okay. Then what we'll do is we'll go ahead and call that scene initializer's update method, or not update, but its init method, and its load resources method. So we'll go into here, we'll say this dot scene initializer equals, or dot load resources, and then we'll pass in the scene. We'll say this dot scene initializer dot init, and we will also pass in the scene. This way we can sort of keep that custom initialization code that we had inside of here and kind of decouple it from the scene itself, because this doesn't really deal with the scene too much. It shouldn't be tied to the scene. The scene is its own thing. Okay, and then we're also going to have to go into here. You'll notice that inside of this init method, we actually declare the camera here. So we'll take that out of there and then put it inside of this init method instead, which should be fine. Then we'll take all this init code. We'll actually just say this is a level editor scene initializer instead. So we'll refactor this, rename it to scene initializer. And this now extends scene initializer instead. And then you're going to notice that this does not have some methods, the init and the load resources. We just have to modify those a little bit. So right now this init method just doesn't take in a scene, so we'll pass in the scene there. And this load resources does not take in a scene, so we will also pass in the scene here. And make this public. And then we'll say at override to make sure that's all working correctly. I'm going to remove all this code now too. We can re-add it later once we continue with the physics engine series. I'm also going to remove all this too. Go ahead and make this private. And this is just a bunch of cleanup too, guys. This is like refactoring. We're not really changing the functionality. We're just changing the way we're doing some things. So instead of loading resources in here, we're going to take that away. And then we're going to initialize level editor stuff right here by saying level editor stuff equals. And then instead of this, we'll say scene.create game object. This should create the game object. Then we're going to go ahead and say level editor stuff dot set no serialize, because we don't want to serialize this. This will be created every time we initialize our game engine. And then we're going to want to go ahead, and we no longer have the camera here, so we're going to say scene.camera, and that will get the camera from the scene. And then we're going to go ahead and remove this start method, because now it's actually going to be started by the scene itself. Okay, so, and then lastly, we just have to say scene.add game object, and then we'll add the level editor. Okay, so this will basically just create that game object initially and then add it to the scene so that we have the same functionality that we did before. And then it will get updated inside this update loop instead of us manually updating it like we were before. Right here, we're just going to say scene.getGameObjects for now. This will hopefully be changed in the future because I really don't like that. So we'll just go over here, right above the getGameObject, we'll say public list of game object, getGameObjects, and return this.gameObjects. That way we can still do this, and that should be fine. And then inside of this update method, we actually no longer need this update method at all, so I'm just going to remove that from the level editor initializer. And then the ImGui method should be fine the way it is. We shouldn't have to do anything fancy there. Okay, cool. So now the scene has the scene initializer thing, and it should call all the correct parts of it. We just have to make sure that we call it inside of our ImGui function as well. So we'll say this.sceneinitializer.imgui, and that should call it inside of the ImGui function as well. Okay, let's run this and see if we have errors, which we do. Let's remove this line because that's no longer valid. run it again. Okay, and then this is where some more of the big changes will happen. Instead of passing in a number, we'll pass in a scene initializer. And so basically, if you want to start the engine, instead of doing all this stuff and just having a preloaded scene, you can pass in your own initializer, which will sort of do everything for you. This is also taking steps to make it so that this engine is going to be able to be extended in the future, right? Instead of us defining exactly the way the engine starts and everything, this will be more like an API that somebody could use and then just sort of use like a library and start the engine with their own stuff, as long as they extend this method. Okay, so inside of this method, we're going to say if current scene does not equal null, and we'll say destroy it, but we don't actually have the way to do that right now, so I'll just leave that as is. And then we're going to say current scene equals new scene. And then we're going to pass in the scene initializer. Okay, so this way we have that scene initializer, which will get called whenever we call these methods. It will implicitly call the scene initializer's load resources and init. So if you're a user of the engine, you should be able to call it. Okay, if we run this again, we now need a scene initializer here. We'll just say new level editor scene initializer. Run this again. Okay, and then we get a exception. And we get a concurrent modification exception. The reason we're getting that is because if we go into our gizmos system or gizmo.java, I'm not sure. I think it's this one. If you notice, the start method is actually adding components, and so we get a concurrent modification exception there. And the way we can deal with that is basically just by going back to where the error happened, and instead of doing our loop like this, we can just say for int I equals 0 and I is less than gameObjects.size I++. This way, if anything is added, then it will not throw an exception. And it should still work the same way too, because we don't have to worry about it. It will be pushed to the end, and then we will still end up starting the new object that was added. You do have the possibility, I guess, for infinite recursion here, but we'll think about that later. Okay, so we'll say gameObjects.getI here, and this should do the same thing. And then if we run this again, we might get some more errors. Nope. Okay, cool. And then we get our project back, and it works, and we can still do everything that we were able to do before. All right, so we've just refactored a bunch of code, and you may be like, why the heck did we even do that? And the reason is, like I said, we're future-proofing for when we make this more of a library. People should be able to use this pretty easily and load their own resources, and then have their own ImGui stuff if they want to, and then have their own initialization code if they want to. Okay, so now what? So now let's actually try and get the physics to start when we press the play button, right? And in order to do that, we have to fix another problem, which is serialization. We need to be able to save the game state right before so as soon as we hit this play button, I'll show you what I mean. When we hit this play button, we don't expect it to stay like it is afterwards. When I hit the stop button, I expect it to go back to the way it was before. Well, how is this accomplished? The way I'm doing this is I'm literally just saving the whole game right before I hit the play button, and then loading that file back in once we hit the stop button. So in order to get this to work correctly, we need to do a little bit more to the scene, which is another reason we just did all that refactoring, in order to get it to load levels and play levels and not cause any memory leaks or anything like that. So one of the things we'll need to do in order to be able to do this is basically when we press play, we destroy the scene that we just had, and then we load a new level, right? So inside of our scene class, what we'll do is we'll create a new method, and we'll just call this destroy. And this will basically just destroy whatever the scene is, okay? So we'll call this destroy. And the way we'll do this is we'll just loop through all the game objects, geo and game objects, and then we'll say go.destroy, which is not a method. So we will create that. Let's go into game object. And we'll scroll down to below the initialization, and then right here we'll have a public, actually go up here, public void destroy, and this will set a flag, just basically say this dot is dead equals true, and then we'll say for int I equals 0 and I is less than components dot size I++, and then we'll say components dot get I dot destroy, and this flag we'll just create up here, which is basically say right below do serialization, we'll say private boolean is dead equals false, and then we'll have a public method down here that just returns that. We'll say public boolean is dead return this.is dead. Okay, now we need to create the components destroy method. So the components destroy method literally won't actually do anything. It's just there in case you need to override it and do any sort of custom work. So let's go into Control-Shift-N component, and then we'll just create a public void destroy, which can be overridden if you need to do any extra cleanup work when the game object is destroyed, or when the game is running and maybe it gets destroyed, you want to play a sound of like the game object's death or something. And so you would need this destroy method to be called, and then you can say, hey, play this sound, you know? And so that's another useful feature for what this is used for. So you may be like, okay, well, when we call gameObject.destroy, that's not actually doing anything because it just sets a flag that says this is dead now and doesn't really do anything. So how do we actually kill it? Inside the scenes update method, we can add in a check to see if the game object has died and then kill it if it has. So inside the update method, we're going to do something similar to what we just did. We're going to say int for int I equals 0 until I is less than gameObjects.size I++. And then we'll say gameObject go equals gameObjects.getI. Then we'll say if the game object is dead, we want to remove it. So we'll just say gameObjects.remove the game object position I, because that is the game object that just died. Then we'll say this .render .destroy game object, and then we'll pass it in the game object. Then we'll say this .physics 2D, which we don't actually have. So let's go ahead and go up here and create a physics 2D object, private physics 2D, and then we'll call this physics 2D. And inside of the init method, we'll just go and initialize that in a minute. So anyways, we'll go into the physics 2D and say destroy the game object go, and this will also kill that game object, and then we'll say I minus minus. And the reason we do this I minus minus is because we're looping forwards through this array, but then all of a sudden we're removing whatever we were just on, so we want to go back one. That way we make sure we don't skip any game objects, okay? So let's go into the render and create the destroy game object method. If we go into render, and then actually go into the render class, we can go ahead and add in a public void destroy game object method here, which takes in a game object. And we'll say if go.getComponent sprite render.class equals null, we'll just return, because that basically means that we don't actually have this game object, right? If it doesn't have a sprite render, we're not rendering anything. And we'll update this to include like font renders and stuff once we get to that. Then we'll say for render batch in batches, if the batch can destroy the game object, then we'll return. So we'll create a method. We'll say if batch.destroy if exists game object, then return. And this basically returns true if it did actually kill this game object because the batch had it, and it returns false if it did not. So then inside render batch, we need to go ahead and create a destroy if exists method. So I'll go right below the render method and then just create a public boolean destroy if exist game object go, and this will say sprite render sprite sprite equals go.getComponent sprite render.class. So we get the sprite render real quick, and then we'll say for int I equals 0 until I is less than the number of sprites I++, and we'll say if sprite I equals sprite. So if this is the game object sprite, then this is the one we want to remove, because we actually have this game object and just got destroyed and we don't want to render it anymore. So we'll say for int j equals I until j is less than number of sprites minus 1 j++, and this is basically going to remove this sprite by overwriting everything. So basically the array will look like this, where each of these are like a different game object, ... And what we're saying is, oh, hey, we want to remove object 3. Well, we could do this pretty easily by just saying, okay, 1, 2, hey, this is object 3. Well, then let's just overwrite it with object 4. And so we'll just move object 4 back, and we basically do this. We just move everything back one. So then we say, oh, 4, 5, 6, 7, and then continue on. That removes the object, and then it makes sure that all of our sprites are tightly packed in that array. So that's what we're doing here. We just say sprites j equals sprites j plus 1. And then we'll say sprites j dot set dirty, which is not a method right now. We'll add that in just a second. Then after we do that, we'll say number of sprites minus minus, and then we'll return true. The reason we set all these as dirty is because this way we can just re-upload all that data and make sure that we actually stop rendering the object that we just removed. So let's go into our sprite render real quick and add that set dirty method, which is pretty simple. We just say public void set dirty, this dot is dirty equals true. Nothing too complicated there. That should remove it from our render, and then we return true if we found it. If we didn't find it, we just make sure we return false. That way the render can destroy it if it exists, and that way our scene is happy because now the render can do it. Now the physics 2D, we need to do that too. So let's go into physics 2D and actually go into the class. And then right here below create game object, we'll create a method destroy game object GO, and we just need to make sure to tell box2D to remove the game object if it has it too. So say RB equals to get component rigid body 2D to class. If RB does not equal null, then we'll say if RB.get raw body does not equal null, which means that it is still in box2D. We want to make sure to remove it. We'll say world, which is box2D, dot destroy body, RB.get raw body. So we destroy it, and then we say RB.set raw body to null. That way we don't try to use it again, because now it would be garbage data anyways, and that would be worse than if we don't do this. So this will just make sure a bug gets thrown if for some reason we try to use this raw body after it is destroyed. Okay, now that successfully removes it from the physics, and now our scene is completely happy, and we have a way to remove dead game objects. So now we can destroy game objects. Why did we do that? Well, we did that because we need to change the way we save and load. So I'm going to change this method from save exit to just save. Okay, because this is now just a saving method. It's not saving and exiting. We could save at any time. And then the remainder of the method is actually going to stay the same. We might change this to take in like a file path and then save it over a file path, which we probably will do pretty soon. But for now, we'll leave it as is. And then the load, we will leave the same as well. And inside of the add game object to scene method, we just want to make sure that we add it to the physics too. So we'll say add here. This way, we actually add it to our physics engine when we're adding game objects to the scene. And then same thing inside of the start method. We'll say this dot physics2d dot add the game object. This way, we basically add it to the physics if we're actually running the game. Okay, and now we're going to make a couple more events to save and load levels. So let's go into our event system. So we'll go into event type actually. Okay, and we actually have these. So we have the save and load method or event types, and we actually want to use those now. So if we go into our window class, we basically just want to go down to where we get notified of events. And instead of saving when we exit, we're no longer going to do that. We will still load it when we come into the scene, but we will no longer save. And then down here, we'll say else if event, and actually we can switch this to a switch statement because this is better suited for this anyways. So we'll just switch on event.type and then say case game engine start play. And then we'll copy this and just paste that. Break case game engine stop play. And then we'll just break and then we will paste this. Then we can remove this code. And then we'll say case load level. So if they want to load the level, what we'll do is we'll just say window.change scene, new level editor initializer. So we'll just literally change the scene again, which should destroy the old scene, which we'll do in a second. Remember, we put that there for a reason. And then right here, we'll say case save level. If they hit that, then we should do current scene.save, and that should save the scene. So up here, when we are creating or initializing right here, we put this comment, destroy it. So when we change a scene, we will make sure to destroy the old scene. So if there is an old scene, we destroy it, remove everything, and then we load the new scene. And then right here, we also want to make sure we get the ImGui layer and set the active, well, get the properties window, and then set the active game object to null, which we don't have right now. This will basically make sure that if we did have an active game object, since it just got destroyed, we won't have any errors from that. And so inside of this properties window right here, we will just scroll to the bottom and say public void set active game object go, this dot active game object equals go. Okay, and that way we can set it to null and all that good stuff. Let's run this real quick and just make sure we can still load, and we cannot. So what is the problem? It's saying this add to the physics is not working because we never initialized physics, right? So inside of here, we want to make sure to initialize everything. So right after we say the initializer, we'll say this dot physics 2D equals a new physics 2D. And then we'll say this dot render equals a new render. And then we'll say this dot game objects equals a new array list. And then we'll say this dot is running equals false. We previously had, some of that stuff up here. Let's just remove it. There's no reason to initialize them here when we have a constructor. Better to keep everything in the constructor just so that we know what is happening, and then remove that as well. Okay. And this level loaded thing looks like we're never actually using it. So we can just get rid of that altogether. Okay, even better. Sweet. So let's see if this works now. Let's just remove that. We weren't using it anyways. It doesn't matter. Okay, cool. So we can still load the scene. That's good. Now I'm going to do something a little bit different than I did before. And that's, I'm going to do basically what the Cherno, if you've watched his tutorial series, was doing. And I like his idea better than what I was doing before. Don't know why I didn't think about it before. We're going to add in another update loop in here. And we're just going to say public void editor update float delta time. And basically this is just the editor update. And that's all it is. So we'll say camera.adjust projection. It's basically going to do the exact same thing as everything in here, except we will not call the update on the game object. We will call the editor update on the game object, which we do not have, but we will. So let's go into game object. I'm completely improving this too, so I have no idea if this is going to work right or not. We will find out. Okay, so inside game object, we will add in another method, public void editor update float delta time. Copy this, paste it, basically do the same thing, except we call components dot editor update, and we can do all of our editor updatey stuff in there. So let's go into components and component, and then we will add in a method right here, and we'll just call this public void editor update float delta time, which can be overridden, and we can do stuff in there. So for example, right now in the sprite renderer, wherever that is, inside the components, so the sprite render, here we go. We have this update, and we will probably just want to copy this and paste it because this is the same whether we're doing editor update or just regular update. Okay, and then let's hit Shift F10. We're going to have some other problems though. Yeah, so for example, this is being weird. And I think I know why, but I'm not completely sure. So let's go into the translate gizmo. We have all this stuff. Let's just change this to editor update instead. Because this is really should only be called in the editor when we're in the editor. And then I'm going to go ahead and go to the scale gizmo. Do the same thing here. Go to the gizmo system. We're going to change this to editor update as well. So basically we do this only if we're in the editor. Let's go to gizmo and then also change this to editor update. And I believe that should be it. So let's see if that fixes that first problem we had. So if we go into here and click, no, that did not fix it. That made it worse. So, oh, and we're never actually calling editor update. That's why it's not working. Let's go into window. And then basically we will go down here. Actually, we'll go up here first and we'll just say private. We'll just make this Boolean is editor play, and then we'll initialize that to false. This will basically just be like to let us know if we're playing in the editor or if we're playing the runtime, right? So actually we could just call this runtime playing, and runtime playing is false by default. Then inside of our loop we could just go and We do this by default, but we can say if runtime playing, then we'll use the regular update method. Otherwise, we will use current scene.editorUpdate dt. Okay, that's good. Then we can go into our onNotify method, and when we start playing, we'll say this .editor or runtime playing equals true, and when we stop playing, we'll say this .runtime playing equals false. This way, we can basically control whether we are playing in the runtime or not, and then we'll update accordingly. Let's see what happens now. Okay, so good news, maybe? I don't know. We lost our grid lines, and I think that's just because if we go to mouse controls and change this to editor update, that should be good. And then if we go to grid lines, if we change this to editor update, that should be good as well. Let's see what happens now. Okay, we got our grid lines back. That's good. We're not getting our gizmos still. Let's go to our editor camera as well, and then just make sure we change this to editor update. That way the editor camera works, and then try and get our gizmos working again real quick. So let me debug this real quick, and I'll let you know what we have to do to get that working. Okay, and the fix was actually pretty simple. I was just missing a line of code. So inside of translate gizmo, change this. This was update. Change it to editor update. Just make sure we update the correct function, and then do the same thing inside of the scale gizmo. And we should have all functionality back. So we can do that. We can scale. Cool. That works. Okay, cool. Next thing, let's go into our gizmo system, or just our gizmo class. And then basically we'll say @override public void update float dt. We'll say if using, and if we're using it, we want to make sure we are not using it. So we'll just say this .set inactive, which right now, what does set inactive do? It sets this active game object to null, and then it hides the gizmos. And then, yeah, I think that should be it. That should all be all we have to do. So now if we go back into our game, if we hit play, the grid lines disappear. If we click the object, the properties show up here, but the gizmos do not, which is good, I think, because we don't want to be moving them around when the game is playing. If we hit stop, the gizmos pop back up. So if I click this and hit play, then hit stop, it pops back up, and it's actually working for that game object as well. Oh yeah, that's because we're not saving and loading the scenes and stuff yet. Okay, so let's also do this. So when we play and stop the scene, if we go into the window, we want to make sure that we save the state and reload the state. So on game engine start to play, we want to make sure that we save the scene. So we'll say save. And then we want to make sure that we say change scene, new level editor initializer. The reason we do this is basically just a reset. So we say, okay, save the scene, then completely reset, except now we can reset with the runtime playing. And do we actually need to change the scene? Yeah, I'm going to say we do. Okay. Then when we stop playing, we definitely need to change the scene, because this makes sure that when we change the scene, we will reload, and then we should reset state. Reset to the state that it was right here. So if physics is playing, once we stop playing, then it should reset. So let's just run this and make sure that if I hit play, okay, and we get an error. So what is this big recursive error? Looks like we had a Stack Overflow. Yeah, Stack Overflow. Okay, so I just restarted the engine and it's not doing it anymore. So I have no idea why I got a Stack Overflow error. Maybe you guys didn't. Hopefully you didn't. But now if we play and stop, everything seems to be working correctly. Okay, that's strange. Whatever. Let's move on. Okay, so if we go into the scene now, we should be able to finally start the physics. Okay, so if we go into the scene class, scene right here, inside of the editor update, that all looks good. Then inside of the normal update, we'll say this.physics2d.update. And hopefully this will be magical and everything will work correctly. I have my doubts sort of, but we'll see. Okay, so if I go into this guy and I'm going to add a rigid body and a box collider, we need a way to see this box collider real quickly. So let's go into rigid body, or actually let's go into box collider. I don't know why I said rigid. Yep, so we'll go into here and then we'll just say at override, so the box 2D collider, override public void editor update float dt, so that we can see the box collider when we're in the editor. And then we'll just say vector2f center equals, and so these are the numbers that I got to make it match up with box 2D. New vector2f, this dot game object transform dot position dot add offset get offset, this dot offset. Well, I have to go into the collider real quick. Let's make this protected. All right, go back to the box 2D collider. Okay, this dot offset dot x and then offset dot y, and we don't even need to do that too. I don't know why I did that, so just add this dot offset. Okay, so that's the center. Then we will say debug draw dot add box 2D center, this dot half size, this dot game object dot transform dot rotation. All right, let's see what goes on now. So if I click this, can't see a green box. Oh, it didn't save it. We didn't save it. We just removed the save on exit function. We'll fix that in a minute. We should fix that now. Okay, so we need a way to save now, right? Let's just add that in very quickly. We'll go into editor, create a new class, call this menu bar, and then we're just going to say public void ImGui, ImGui.begin main menu bar. And then we're going to say ImGui.end main menu bar. Then I'm going to go in here and say if ImGui.begin menu, begin menu. And we're going to call this file. We're going to say if, first of all, ImGui.end menu in here. That way we don't get any errors. Then we'll say if ImGui.begin menu item, or I guess it's just menu item. Save. We're going to go ahead and say shortcut is Control S or Command S, which we'll do later. And we'll actually implement that later too. Right now it's not going to actually do anything. But anyways, we'll do that, and then we'll just say if this happens, event system dot notify null new event, import that, and we'll say event type dot save level. So we'll just send that event, and then we can say if ImGui.menu item load, and then we'll say control plus open. So this will technically be open later. So control O. Then we'll say event system.notify null new event type dot load level. And then if we go into our ImGui layer, which is inside of Jade, right here, ImGui layer, right here is where we'll basically be doing the menu bar. So I'm going to scroll all the way to the top, go up here, we'll say private menu bar, and we're going to import that from the editor. Then inside here, we'll just say this dot menu bar equals new menu bar. And then we'll go down to where we're updating those two, which is right here. So right after we do the properties window, we'll say menu bar dot ImGui. Okay. Now we should be able to save and load our scene. So if we go here, we'll add a rigid body, add a box collider. Let's see if we can see the box collider. So I'm going to say half size, stretch it. Oh, yep. And you see it down here. So it is working. I'm just going to make that bigger. Hit file save. If we reload this now. Okay, cool. It's kept the box collider. Now the important part, if we give it a mass, we'll just increase that. Press play. Okay, and then we get a big error. And it's this weird thing again. Okay, and what was the problem? I can't believe I didn't think of this. It's inside a rigid body. So go into the rigid body class in our file. Make the body transient. We don't want to save this because this is not, we're not under control of how this is created and stuff. I believe that's what was causing that problem. So now if we go into here and add a rigid body and a box collider, if we hit play, stop. Okay, cool. So look at that. It's falling. This is amazing, right? So if we go into this rigid body now, up the mass, hit play again, it's going to fall the same speed because, you know, gravity. But if we hit stop, it goes back to its original position and everything. Right now, if you actually create the box collider, you're probably going to get problems. So if you actually created this and did some other boxes, you will get problems. And we will fix that in the next tutorial because this has gone on for way too long. Okay. So I hope you guys enjoyed this mega episode. If you did, please hit like and subscribe. But yeah, we're making some really great progress. We have this whole play stop. We have our editor runtime. We have our runtime. And we have sort of the concept of both. And we have physics working, which we'll have it completely working in the next episode, sort of. So in this episode, we will finally be getting to the point where we have this, where we have Box 2D fully, quote unquote, integrated, and we can actually create physics bodies and play and stop our scene like this. Now, to get this done, we have 3 big things left that we have to do. First thing, we need to fix the rotation so that it rotates about the center of an object instead of what we currently have it where it's rotating about this corner. Second, we have to add support for enums in our Box 2D code. So right now we have an enum here, but we can't switch it because ImGui, the code we have written for ImGui, doesn't know how to handle the enum. So we will add support for that. And lastly, you'll notice that the scale on this object is very small. So the scale is 1.05, whereas before we had it at 32. We'll be resizing the projection matrix and the camera's viewport to be a much smaller viewport because Box 2D works best if you model it after real world units in meters. So that means that if we have a box that is 0.25 meters, it should be reflected in the scale, and that will make it behave more realistically, like better physics in general. If you have it too big, then it can get weird, and if you have it too small, it can get weird. So we're just going to be resizing it so we can have better units to work with. Okay, so let's take a look at how all this is going to work, and then we'll go ahead and implement it. Alright, so like I said, we have 3 big things that we're going to be doing in this episode to get our project to the state that I showed in the beginning. The first thing is we have to resize our projection matrix. Right now, the way we have our projection matrix sized, it's more like it's 1920 by 1080. So this is like 1920 fragments. I'm not going to say pixels because technically it's fragments. And this is 1080 fragments. And what we're going to do is resize it so that this is now 6 fragments and this is 3. This way it'll be more like the camera has a viewport width of 6 meters by 3 meters. And in the future, we'll probably make this customizable so that if you place a camera in the scene, you can decide how wide and how tall you want that camera to be. Okay, so that's pretty simple. We're just going to change the projection matrix. We'll have to fix a few other things to get the grid lines to work properly and stuff like that because now they'll be different than going 32 by 32. Second thing that we will be fixing is enums, right? So if we put an enum inside of some sort of script, like say you have a player script and that player script has an enum called state, and that state enum has value 1, value 2, value 3, etc. Well, if you want that to be choosable at runtime in the editor, right now it's just not going to show up because in our ImGui function for components, we don't have a way to deal with enums. So what we can do is we can check and see if we have a value that is an enum using Java reflection, and then we can even iterate through each of the values, display them inside of the ImGui window, and then we can allow you to choose them by choosing a specific value. And so we'll take a look at how to do all of that and write the code in ImGui to get this working, which is a pretty cool feature to have. And then when the player has some sort of script that has a state enum, it'll just automatically detect the different values and stuff. Pretty cool. And then lastly, what we have to do is we have to fix the rotation. So right now we have it so that if you were to rotate any cube, it would sort of rotate about this axis, and then it would be like over here now if that was the same cube if we were to rotate it. But what we want to happen is we want it to be rotating about the center just because it makes more sense to rotate something about the center. And once again, this might be customizable in the future, but for now, we should have it rotate about the center because that's more intuitive. To get that to work, inside of our batch render, what we currently have is we have these values where it's like 1.0. So we go like 0.0, 1.0, 1.0, 1.0, etc., etc. And this basically says, hey, add this to whatever vertex. So if you specify this position, then this will be the bottom left corner of whatever object you're drawing here. Whereas we want you to specify this position, and then the vertices go halfway across to each of those. So instead of using 0 to 1, we'll just use negative 0.5 to 0.5 in our batch render, and that should fix the issue of it showing up in the wrong sort of way. Okay, let's get started with the camera projection, and then we'll get all this stuff working. All right, guys, so first things first, let's fix our camera's projection matrix. So if we go into here, into our project, okay, and then when we go to camera, then we can go ahead and just fix this. So instead of going 32 times 40, 32 times 21, we want this to be 6 by 3. All right, and we'll actually parameterize this too, just so that we know that this is a parameter. We'll say private float projection width equals 6, private float projection height equals 3, and then we'll just copy and paste this into here and copy and paste this into here. All right, so now our projection should be fixed. If we hit Shift F10 and go back in, you'll notice we don't see any grid lines or anything. Why is that? That's because our projection has shrunk. So to fix that, if we go into grid lines, we can see that basically what we're doing is we get the grid width and we want to change this width because right now it's 32, which is way too big. So if we change this to 0.25f, which I found out is like fairly reasonable width and height, and then change this to float, we can change the grid size. And if we go back into grid lines, this is going to create some problems. We just change these to floats, and this will fix all of these issues. So just change all of these types to float, and that should be fine. Then if we run this again, we get our grid lines back. But when we drag and drop an object, this is huge. Okay, so this is the object, but it's huge compared to our projection. So we want to fix the scaling now, and the way to do that is if we go into prefabs, we can see this is where we're actually creating that object, and we can see that we set the size to whatever size, and it's using this function. Now, to find out where this function is being called, because it takes a size x and size y, we can just right-click the function and say find usages. Then we'll go into here, and we will go ahead and change this. So instead of doing 32 by 32, we'll do 0.25f by 0.25f. Now that should fix the sprite object, which if we click this, okay, it is normal size now, but the gizmos are super huge. So if we actually look at that find references function, it also said the gizmos weren't right. So if we go to gizmos class, then up here we have the width and the height and everything, and actually copy the width right now and paste it over here because for some reason we never had it using the actual width and height from up here. Anyways, that will get the correct width and height, and I found that if we divide by 80, it gives us some good estimates of how to shrink this. So if we change this to over 80f as well, and then if we just change these to floats instead, then that should be good, and we now have a good size gizmo. But we're going to also have to change the offsets because these are messed up now too. And I found out that 24 over 80 and minus 6 over 80 was good for this one. And then for this one, I found out that minus 7 over 80 and 21 over 80 was good for this one. And this isn't going to look right immediately. That's because we still have to fix the batch render. So if we drop this in, they look kind of weird. This does not look right at all. And that's because of the next thing, which I said, we basically want them to rotate about the center, which was the next phase inside of the things we have to fix, right? We want it to rotate about the center instead of the bottom left corner. So if we go into render batch, we can fix this real quick just by going down to our load vertex properties function. And you can see that this is where we have the xat equals 1, 1, and then 0, and we're using those. We can just change this to 0.5 instead, and this will basically place things about their center instead of placing them by the lower left-hand corner. So if we change this to 0.5 and minus 0.5, and this one to 0.5, then we load this back in. The gizmos should look fine now. So if we hit the gizmos, they look fine, but their bounding boxes are off, and that's because now we're placing them about the center instead of placing them about this left-hand corner. So if we go back into gizmos, where we have the check X hover state and check Y hover state, we can just fix this by adding in half the width. So if we go ahead and say plus gizmo height over 2.0f, and then we subtract half of the gizmo height, and we just do this for everything, then we should be good. So we'll say minus half of the gizmo height over 2.0f. We'll copy that, paste it over this. Wait. Nope, this should be gizmo width. So make sure that's gizmo width, and then if we copy that and we paste it over this guy, then we should be good. And then if we copy this, paste it right here, and we'll say this should be minus, then that should be good as well. And then we do the same thing for the check Y hover state. So this should be plus gizmo width over 2.0f, and then just copy that, paste it over here, and this will now be minus. Nope, I'm sorry, this is still plus, so then this will be plus. And this should actually be gizmo height, and then we can copy that, and we can paste this over this, copy this, paste it over this one right here. Okay, there we go. So now that should fix the bounding boxes of what we're checking. So if we drop in an object, click it, you'll notice that the bounding boxes look like they are fitting it appropriately now. So that's good. This is working fine now. And you can take a look at these, pause it right here if you want to take a look at those. Now the next thing we want to fix is inside of the components, because right now if we were to drop an object into here, and notice also how it's going about the center, so it's not lining up with the grids perfectly, and that's because we are placing it according to the center now instead of according to the bottom left, which is good. But anyways, if we go into here and we hit add rigid body, you'll notice there's no drop down for, if we go into rigid body, for the body type, which we do want there to be a drop down for that, because that's the best way to represent this. So to fix that, if we go into component, we just need to add in a else if inside of our big component ImGui function. We just need to add in something for enums. So if we say else if type dot is enum, which Java conveniently gives us, and then we can say string, then we'll say enum values equals get enum values type. This will basically get each of those enum values as a type. So if you have an enum and it has like value 1, value 2, dot, 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 basically it will return these values as strings, and we can do that using reflection, and we'll create that function in just one moment. And then we'll say string enum type equals enum, we want to cast it to an enum value dot name. Basically what this does is it converts whatever the enum's actual name is to a string so that we can use it right here. And then we'll say ImInt index equals new ImInt index of, which is another function we will create, enum type, enum values, and this will basically get what the index of this type is, this string within this string array, which will give us all the information we need to then say if ImGui.combo, and we want to use the enum, whatever this field's name is, so field.getName, and then we want to say index, because if we look at this, this says, okay, what's the current item? The current item is index, and then the items are the enum values, and then we want to say enum values.length for the index count. So if that is true, so if they changed it, then we say field.set this to type.getEnum constants index.get. And basically, if you control click on this, this says that it gets you an object array, which is basically the enum, and it gets you an array of all the enum values. So we basically set the enum to whatever its appropriate index is inside of this enum array. Okay? A little bit confusing, but I promise it's not that bad. If you take a look at the code a little bit deeper, you should be able to get this pretty easily. Now let's create this getEnumValues function. So if we scroll down, right above the destroy method, we will go ahead and say private t extends enum t string array. So this is going to return a string array, getEnumValues. And we want to say class t enum type. So this looks very complicated, but it's really not that bad. We're basically saying type t is a type that extends enum. So it is, we're saying this type needs to be an enum. It needs to be an enum, okay? That's what we're saying. And then we want to say we're getting a class that is this type. So this restricts this function to only be able to be used if the type is actually an enum, which is good. So if you try and use this function with something that's not an enum, it will throw an error. This also gives us useful hinting information. So then we can say string enum values equals a new string enum type dot get enum constants dot length. And we can get the enum constants off this type because we know for sure it is an enum. Then we'll say int I equals 0 for t enum integer value of enum type dot get enum constants. So we're going to loop through each of the enums as integer values in the enum constants. Technically they're objects, but it is what it is. We'll say enum values I equals enum integer value dot name. And this will do the same thing that we did up here, which basically just gets the name, so the actual value, the variable that you named it, okay? And then we'll say I++. Then return enum values. All right, and then the second function is much simpler than that one. Private int index of string str inside of a string array. And this will just loop through. We'll say for int I equals 0 until I is less than array.length I++. Then if string dot equals array I return I. Otherwise we return -1. So we just loop through the array, and then if we find something that matches the string that they passed in, then we return that index. Otherwise we return -1. Very simple, nothing too complicated there. And now this should add support for enums. So if we compile this and run, and we add a rigid body, we can now get the body type. So it says body type, which is what we call the variable, and we can change it to the different enums. And this is all generated automatically. So to illustrate just how cool this is, let's go into rigid body again. If we click on body type and then we add in something new here, a new value, then we recompile, you'll notice that if we add this in and we click it, add rigid body, we get a new value down here, just dropped into that drop down. Super cool stuff. This is why reflection is so awesome, and we can use it to do very cool things. All right, cool. So now that works. One thing we need to fix also, if we drop in an object here and we try to change the transform's rotation, it doesn't do anything. Why doesn't it do anything? Because I was stupid when I created the transform class and forgot that this returns a float and this returns an int. So we need to say this dot rotation equals that, and we need to say this dot zindex equals that. Now if we run this again, that should be fine. So if we run and change the rotation, we can rotate it. Also, notice how it is rotating about the center of the object. That is very cool. We can rotate things about the center. Right now, we're at a really good place. If we add a box collider to this and then actually set this to like 0.25, set this to 0.25, and then if we go ahead and give it a rigid body and just leave everything as is, then we add in another object down here. We'll say give it a rigid body and a box collider. Change this box collider also to 0.25, 0.25, not 0.14. And then if we just make this one static, static means this one won't move, dynamic means this one does move, and then let's give this one some mass. If we hit play, it works. We have physics, look at that. That is very cool if you ask me. If we move this over and hit play, it bounces off the object like it should. Cool. So we've basically got physics working. Now, what would be nice is if we could hit Control D and duplicate this, because right now in order to add in a whole new object, you actually have to drag this in, change everything over here, and that's quite annoying. So let's add in an option to duplicate very quickly. If we just go into Gizmo, and the reason we're putting this in Gizmo for now is because it has this whole active game object. I do want to switch this in the future. I don't like the way that this was done initially, but for now, this is how we're going to do this. We'll just add in a key binding. We'll say if key listener is key pressed, and then we'll say GLFW key left control and then I'm going to move to a new line. Key listener dot key begin press, and this is a function we will add, GLFW key D, and then let's import that. So what is key begin press? Well, basically this just means if they press this, we'll trigger this the very first time, but if they hold the key down, it will not return true. So this will return true for the first frame where this is pressed, and then every frame thereafter it will return false. How do we implement this? Well, let's go into key listener. If we just go ahead and create a new Boolean array up here, key begin press equals a new Boolean, and we'll make it the same size, 350. And then if we go ahead and just go down here and say get.key begin press key equals true when we press it, and then get.key begin press key equals false when it's released. This will basically just set this value to true the very first frame that this is hit, and then it'll set it to false whenever it's released. It won't set it to true if the key is being held down. Then we'll create a new function. We'll say public static Boolean key begin press int key code. Then we'll say Boolean result equals key begin press. Well, we have to say get.key begin press key code. We'll say if result is true, then we want to just set it to false. Then we'll say get.key begin press key code equals false, and then we'll return the result. What's happening here is we're basically just saying, okay, if they query this and then it turns out to be true, and then we're just going to set it to false. This could pose problems for, like, if multiple people ask for the same key, then this technically won't work correctly. We'll fix that in the future, but for now, this works as it should, and we'll look into fixing that in the future. Okay, let's go back into Gizmo to get this working now. So if the key is begin press, all that stuff, then we should be good. And then what we're going to do is we're going to say game object new object equals this dot active game object dot copy, which we will create. And I'm also going to put a to do in here too, because I don't like this. We'll say right down here, to do, move this into its own key editor binding component class, because that's where this stuff should be. This shouldn't be stuck in like gizmos, but we'll have to fix that later. So we're going to copy the object, then we'll say window.getScene.add game object to scene, the new object that we just created, and then we're going to offset it a little bit so that's not directly on top of the old object. So we'll say new object.transform.position.add, and then we'll just say 0.1, 0.1, which will basically just add a tiny little offset so that's not directly on top of it. And we'll say this dot properties window dot set active game object to that new object, and then we will return. So now if we were to do this, then we should be able to copy once we implement this copy function. So let's go into game object, scroll down, and let's create a very quick and dirty copy object. So we'll say game object copy. And I don't like the way we're going to do this, but we're going to do it nonetheless. And we're going to put a to do in here. Come up with cleaner solution, because it's ugly, but it works. And that's how we'll use it for now. Let's go into scene. If we go into scene, we already have a way to serialize and deserialize, which is basically creating copies of objects. So if we copy this code right here to create a Gson object and paste it right here, I'm just going to get rid of pretty printing because that really doesn't matter. Then we're going to go ahead and say string obj as JSON equals JSON.toJSON, and then we're going to pass it this, which is the game object. So basically this is going to serialize the game object into a string, which is right here. Then we will try and deserialize this string. So then we'll say game object obj equals JSON.fromJSON, and then we're going to say the object as JSON as the string we want to deserialize, and then we'll say game object.class is the class that we're using. And then we just have to do a couple things. First, we have to say obj.generate UID. So generate a unique ID for this game object, which we will create a function right here. Public void generate UID this.uid equals ID counter plus plus. This will just generate a new unique ID for this game object. And then we'll go ahead and say for each component, C in obj.getAllComponents, C.generate ID. So we generate new IDs for all the components. Then we'll say sprite render, sprite equals obj.getComponent, sprite render.class. If they have a sprite render, so if sprite render is not null and sprite.getTexture is not null, then we just want to make sure to reset the texture to the appropriate object reference, which we can do by saying sprite.setTexture. Asset pool.getTexture, and then we want to say sprite.getTexture.getFilePath. This will just make sure that we reset that object reference that's pointing to the correct object, and then we'll just return that obj. Okay, so now if we go into our game and we go ahead and duplicate this, we can duplicate it and it has all the same properties as that object. So now if we were to put this here, it should have all the same physics applied, which it does. Very cool, quick and dirty, but it works. Last thing I want to add too is if we go into Gizmo, and once again, we're gonna have to change this in the future, but for now it works. We'll say else if key listener dot key begin press, GLFW key delete. So if they press the delete key while selecting an object, we want to delete that object, so we will just do, we'll just say active game object dot destroy. We destroy the game object, we'll say this dot set inactive. We are no longer using the gizmos, and then we'll say this dot properties window dot set active game object to null, and then we'll return. That should allow us to delete objects as well as add objects. So if we click this and we hit delete, we can remove it from our game object scene, and we can click this and hit duplicate an object, and we can do that, which is pretty cool. And then we can duplicate this one too, drop all these, and it works like you would expect. This is really cool stuff. I think so, at least. Maybe you guys don't. But we have physics working, and we can sort of start building scenes pretty easily. Now, there is one more thing too that I do want to address. If we drag and drop one of these guys in, and we were to move him over this and change his Z index, if we change it to like -3, it doesn't do anything right away. But if we play stop, you'll notice then it changes. We should change this so that it changes immediately, because that's not cool. Basically what's wrong is the Z index is being changed, but it doesn't take effect until the next time we add it to the render. So to fix this, we can just go into our render batch and just add a couple things. This is also kind of dirty. Don't like the way this is done. We'll fix this in the future. So we'll say to do get better solution for this. Basically what we're going to do is we're going to say if sprite.readd, which means that we need to re-add it to the render, which the only reason we would need to do this is because the sprite has changed its Z index, right? Actually, no. Okay, so let's do this. We'll say if sprite.gameObject.zIndex .transform.zIndex does not equal this .zIndex. So if we have a sprite in here that isn't actually supposed to be in here, what we're going to do is we're going to say destroy if exists sprite.gameObject, which clearly it does exist. What does this do? Remember, this basically just shifts all the sprites over it. So what we want to do is we want to make sure that right after we destroy it, wherever that just happened, right here, we want to make sure to say I minus minus, that way we don't skip any sprites. And then we want to re-add this game object to the render. So then we should be able to just say render dot add game object, and then we'll say sprite dot game object. And the way we can do this is very simply by getting a reference to our render. So inside of this constructor, we'll say render, and then we will keep a reference to that render right here. And then we'll just say this.render equals render, and if we run this, we'll get an error because we need to add that right here now. So then if we go move this to a new line, and if we pass this, which is the render, so this is inside the render class, if we pass this, we will pass the render. And then this is saying this isn't a function, so if we just say add, that should add it to the render. Okay, so now if we click this and we say transform, change the Z index, we get an error. What is that error? concurrent modification. So if we click into here, we can fix this pretty simply just by saying for int I equals 0 until I is less than batches.size, I plus. And then we'll say batch or render batch equals batches.get I. If we do this again, we should be good now. So then if we go ahead and move this, okay, cool. Now we can change the z index. Awesome. And then if we change this to an even higher one, it goes in front of that. Cool. Okay. So that was something else that I thought was just important that we should have in there right now. Now, I can't remember if I am forgetting anything, but I think this is it for this tutorial. We've done quite a bit, and it's pretty cool seeing what we can do now. We can build physics simulations and scenes, and it works pretty good. I think in the next tutorial, what we're going to start doing is actually start building a game, because the engine is at a point where we still have some problems, like you'll notice the grid lines aren't really perfect. We need to fix that. And there's some other things that we need to fix. But I feel like for the most part, the engine is at a good point to start building the game. And as we build the game, we'll see the features that we actually need. Hey guys, what's up? My name is Gabe, and this is Games with Gabe, and this is the next episode in the Game Engine series. This episode is really just serving to tell you to go check out the font rendering series at this point. I'm starting a font rendering series because I feel like that's the next logical step for our game engine, and font rendering is such a huge topic that I thought it'd be a disservice just to sort of cram it into the game engine series. So instead, what I'm going to do is dedicate a whole series just to that, maybe 4 or 5 episodes. We're going to go over bitmap rendering, which is like the most traditional form of font rendering. We're going to go over SDFs, which are signed distance fields, and they're like a little bit more of a step up from bitmap rendering with some other trade-offs. And then lastly, we're going to go over parsing TTF files manually and then using the Bezier curve data in there to write custom shaders and stuff, which also has some trade-offs, but it will be interesting to see how all these different methods work so that you guys can choose which one you like the best and which one you would want to use for the engine. So I'll show you real quick the little demos that I have for each of these. SDFs are the only one that I haven't actually implemented myself yet, but for bitmap rendering, we will be creating a giant texture using Java that looks something like this, where basically we just have all of the drawable characters or glyphs. And then using this texture, we can just sort of perform a manual texture lookup, upload this to the GPU, and then sample from whichever character we are trying to draw. Then the second method that we're going to take a look at, which is using the Bezier curve data, we'll basically use a custom shader, and I have a little demo here. And you can see that we can draw all the letters, but what's interesting about this is not resolution dependent. So when I make this bigger, you'll notice that this did not blur. It's still pixel perfect, and that's just because of the way we're using the Bezier curve data instead of using a fixed font size from an image. So this will scale infinitely up and down, and it's interesting. And if we can get this right, I'm still doing some optimizations and stuff, then it will actually take up less memory than it would to upload an actual texture, which is also interesting. But it's slower, and I'm trying to speed it up to see if this could be a viable solution. So we will see about this. We will also be looking at the different metrics involved with font rendering. So you can see here, this is a website that is pretty old, but it has some useful information on fonts. And there's a ton of different stuff that we have to learn about these fonts in order to render them correctly, including things like kerning and placement of the fonts vertically and horizontally to make sure that it all spaces out correctly and looks correct whenever you are rendering it to the screen. So this is why I am doing a whole series on it. It is a big topic, and there's a lot of stuff that we will go over. Anyways, there should be a link in this video to the font rendering series. Click on that, start watching that to see the first episode in which we will be doing traditional bitmap rendering first. So I have Cocoa Engine open up right here because this will illustrate what we will be working towards in the next few episodes. So in the left here, you can see that I have a bunch of different tree nodes, and these tree nodes correspond to these objects. So if I click on one of the objects, you can see it highlights over here, and if I click over here, it highlights over here. So if we click on this group, then you can see he moves himself and his children, which you would expect, and that's good. And then you can also rearrange groups and stuff. So if I wanted to put him as a child in here, I could just drag him into here. Now all of a sudden he is a child inside of here. And if we move him, he moves all of those. And then if we want to drag him out, we can drag him to the line right here, and he is outside of it again. You can collapse the groups, you can rearrange them however you want, and you can click onto them and you can rechild them, reparent them, and it will all work as you expect it to. So that is what we will be working on today. Well, what we will start working towards today. We will not get to this point because this is quite a bit of stuff to get done, but hopefully we'll get here pretty soon. What we will get to today is, you can see we have the scene hierarchy panel over here, and then we have all of our objects over here. So you can click onto them like you could before, you can move the transform, all that stuff, but we also get them over here. And if we were to add a new object, then you can see that it updates over here. Now we can't do all the moving stuff because that takes a while, and so we'll just be getting to this point. So the very first thing that we're gonna have to do, well, first of all, if we remember from last episode, we were at a point where we could now do physics and we have a play stop button and everything. So I believe that's where we left off. And what we're going to do now is work towards what I just showed you there, where we have that scene hierarchy panel just getting started. So the first thing we have to do to get up to here is we have to upgrade ImGui, because the old version will be deprecated soon. So we will not be able to use this implementation of it. So we're just going to remove all of this. We're going to change the version here to 1.81.0, and then we will go ahead and add a new implementation. So we'll just say implementation is io.github.spare imgui-java-app, and then we'll give it the imgui version, which is just like that with a $. And I believe that should be good. This is just from spares imgui, his repository, so it's the same exact thing as it was before. And then we'll go ahead and import those changes. Just make sure that we don't have any other ImGui stuff, so we should be good. We can import those. We should get an import success, so you shouldn't have any errors after that, but we will have errors inside of ImGui layer. So if we go to ImGui layer, then you can see it just started highlighting it because it figured out that we have a bunch of errors. We can actually remove quite a bit of stuff because we don't need it anymore since he has upgraded a lot of stuff for us. So for the fonts, first of all, because we are using a different font, you may or may not be, but we will go ahead and first of all, remove this. We don't need this at all. And I believe that should be good. We shouldn't have to do anything else. So that was really simple. We just had an extra line in there that is now done automatically for us. Another thing we can do is there is a lot of stuff up here. All of these that we can remove now, because all of this is done automatically for us. So we can go up to the keyboard mapping, remove all of that, and we'll go up to here. We will go ahead and remove the mouse cursors because we no longer need that either. And then we'll also add one more thing up here, which is private final ImGui, or actually, yeah, GUI GLFW impl. So impl GLFW. And then we'll just call this ImGui GLFW equals new ImGui impl GLFW. So that will be something else that we need, which will sort of do those things that was done automatically just a second ago. And right here, we could go ahead and say io.setConfig flags, ImGui config flags.viewports enable. But I was having trouble with docking and viewports, and I couldn't figure out what was wrong with that. So I'll show you guys all the steps to set up the viewports, but I'm going to leave it commented out. And if you can figure out what was going wrong, because I'll show you what's going wrong with it too in a minute. But if you can figure that out, let me know so that we can update this and have docking and viewports. But right now it's just not working for me for some reason. And then let's just go ahead and comment this line out because we do want to enable navigation with the keyboard. And we can also comment this line out because that is set automatically, I think. So we should be good without those flags. And then let's go back down to the bottom of this method. And we also want to call, right before we do ImGui GLF3, we'll say ImGui GLFW init. We'll give it our GLFW window. And we'll say for installing the callbacks false because we already installed our callbacks up here. Like this is where we do all our callback stuff. So that's good. Okay, and then we'll take a look right here. I just sort of moved some things around here because it didn't make sense to me the way we were doing it. So instead of doing imgui.newFrame in there, we should do that in startFrame. That just makes a little bit more sense to me. So we'll go down to here, do that right there. And I think we can remove a lot of this stuff as well. yeah, we can remove all of this because we don't need any of this stuff now. So just delete all of that and start frame. And then we'll go ahead and say in here as well, ImGui GLFW new frame, which is the only two things we need. That does sort of the things that was there just a second ago, but abstracted away, which is nice. I'm also going to comment out show demo window. You can uncomment this when you need it, or put a Boolean flag in there so that you can actually toggle it on and off, but we don't need it right now. And then these two things I feel like should be abstracted out too. So ImGui end and ImGui render. First of all, the end was in the wrong place, I believe, altogether, but we'll fix that in just a second as well. So let's go to end frame. We'll drop those into here for now. We actually don't need this. The only reason we had the ImGui end was because of this. We have a begin right here. So instead we'll put ImGui.end right here, which should do the same thing. Now, anyways, inside of end frame, we do have to add a few different things. So we're rendering to a frame buffer, right? So we need to make sure we say bind the frame buffer, GL frame buffer 0, which basically means make sure that we are drawing to, and we'll import all this stuff too as well. But this basically says make sure we're drawing to the window, right? Because frame buffer 0 is no frame buffer. So we're saying unbind any frame buffers currently bound so that we're drawing to the window. Then we'll viewport, so we'll say GL viewport 0, 0, window dot get width, window dot get height. So we're saying set the viewport to the entire window size, which is what we want. Then we will say GL clear color, and we'll give that 0, 0, 0, 1. So we're just going to give it a clear color of black, which doesn't matter because it's going to be drawn over by ImGui anyways. And then we'll say GL clear, GL color buffer bit. Okay, so this just makes sure that whenever ImGui goes to draw, it has a fresh slate. We just cleared it so that it won't be redrawing old stuff. That one took me a while to figure out. Okay, anyways, and then we'll move this up to here. So ImGui render right there. And then we want to do ImGui GL03 render draw data instead of render. Now, the next part you would do if you had viewports enabled and it was working is you would say long backup window pointer, which I'm getting this from the ImGui spare. We'll say GLFW get current context. Then we would say ImGui.update platform windows. And this is from like dear ImGui's GitHub anyway. So, and you would say ImGui.render platform windows default. Then you would say GLFW make context current backup window pointer. So what's happening right here is we're basically saying, hey, get what the current window is. Then we say ImGui update platform windows, because you could have multiple windows with the viewports enabled, right? If you have a window dragged out, like one of the panels outside of the main window, that's a new window now. Then we say render to all those windows, and then we say, okay, back up to the main window. So then it just remakes our current context to that main window. We're going to comment all this out though, because I could not get this to work right. So we'll see what happens when we actually enable all this stuff in just a second. This should be fine. Nothing wrong there. Now, one more thing inside the doc space, if you wanted viewports enabled and you want it to work right, you would have to say ImGui viewport, main viewport, and this is all from dear ImGui. So is ImGui.get main viewport. Then you would say ImGui.set next window pose, and you would say main viewport.get work pose X, and you would say main viewport.get work pose Y. Then you would say ImGui.set next window size, and you probably guessed it, main viewport.get work size X, and then main viewport.get work size Y. Then we would say ImGui.set next window viewport to the main viewport's ID. And so this should basically set it so that our docking panel is our main viewport, but once again, I could not get that to work right. So we'll leave that blank. We'll leave this. We don't need that ImGui cond always. That's fine. And everything else should be good. One last thing I did too was I was having some weird things with the menu bar. It was like taking up extra width. So let's move this into the actual main window here, right? So if we do this between the begin and between the end, this will be in the main doc space window. Then if we go into here, we can change this from begin main menu bar to just begin menu bar. And then we will end a menu bar. And so this will basically make sure that we don't have a weird extra layer or something, which is what I was getting. Yeah, and I think that should be good. So let's run this and just see what happens, I guess. So if we run this, we should hopefully get, cool, we get everything and it's still working the same. So we have now upgraded ImGui, and it doesn't look like if we drag this, yep, we still got docking. Awesome. So what happens if we try to enable viewports, okay? Because you guys are probably wondering like why I have all this commented out. Well, let's uncomment this. Let's uncomment this. And then one last line up here, we will uncomment this. So if we run this now, this is what ends up happening. You get this mess. If you drag, you can't actually drag it into the viewport, and it's pretty laggy. So don't know what's wrong here, but it's just not working right. So instead, we will leave all this stuff commented out, and hopefully there will be a fix soon, or one of you guys will let me know that I'm doing something wrong and that's why it's not working. But anyways, I'm gonna go back into here real quick, fix this back up. So you can see that now if you drag stuff around again, it should work like you expect it to. And then I'm just gonna click one of these guys so that we get this properties window, and I'm gonna dock him up here just so that we have it right there. Cool. So now that ImGui is upgraded, let's go ahead and create that scene hierarchy panel real quick, which is actually a bit easier than you would think. So the first thing we're gonna do is go into our editor and we'll add a new class. We will call this scene hierarchy window. All right, and then we're gonna go ahead and just create one method, which is ImGui. So we'll say public void ImGui, and trust me, this will get much bigger once we start adding in all the functionality, but for now, this is all we'll do. We'll say ImGui.begin scene hierarchy, and we'll go ahead and import that. Then we'll say list of game objects, and we'll call this our game objects, equals window.getScene.get game objects. All right, so we're going to get all the game objects so that we can iterate through them. And we'll say index equals 0 because we need to, if two game objects have the same name, then we could have trouble with ImGui's tree nodes. And then we'll say for game object, obj in game objects, if not obj.doSerialization. So if it's not serializable, then we probably don't want to display it in the scene hierarchy panel. So we'll just skip over it. We'll hit continue. Otherwise, we will actually do the tree node for this, and that's pretty simple at first. It gets much harder, don't worry. We'll say ImGui.pushID. We're going to give it the index, so that way it has a unique ID every time since this is incremented. And as soon as we end this window, then the ID is reset. So it's fine that these are starting at 0. They won't clash with any other indexes that you have in different windows. Then we'll say Boolean tree node open equals ImGui.treeNode EX, which is basically just like the extended version. And we're going to give it the name, which is right now private. So let's go into game object, make that public because there's no reason it should be private. All right, so the name, and then if we hit Control P, you can see the next thing is ImGui tree node flag. So I'm going to indent one since we're going to have quite a bit. And we'll say ImGui tree node flags dot default open. So we're going to default them to open. ImGui tree node flags dot frame padding. That just says make sure you give it the frame padding, which makes it look a little nicer. ImGui tree node flags dot open on arrow. So this means that we'll open it when we click on the arrow and not when you click on it. And then ImGui tree node flags dot span available width. And that just makes sure that it takes up the whole width of the object it's in. And then for the label, we'll just say the name once again. Then we can hit a semicolon. That should be good. And we'll pop that ID because we don't want to keep that hanging around. And we'll say if the tree node is open, then we're going to say ImGui.treePop. And that way you just have to make sure that if this is open, you pop it. Otherwise you will get a stack error. So you get like an error from ImGui saying, hey, you have a mismatched index or something. But yeah, let's go back into ImGui layer. We will add that object as a dependency in here. So we'll go ahead and say we have a private scene hierarchy window, scene hierarchy window. Then we'll go down to here. We'll say this dot scene hierarchy window equals new scene hierarchy window. Then we will just go ahead and call ImGui inside of our ImGui function, which is right here. So we'll say scene hierarchy window dot ImGui. Now, if we run this, we should hopefully get it working. Doesn't look like it was. Oh, and we got exactly the error I warned you about. See, so it says current window stack size equals 1, mismatched begin. Oh, this is a different error though. So this is, look at your errors, be cognizant of what it says. Look, this says mismatched begin child versus end child. Did you forget to call end child? Okay, so he's telling us exactly what we did. Look, I have ImGui begin here. I never call end. So I missed an end call. All right, so now if we hit Shift F10, there we go, we get it, and we get this scene hierarchy window, which we can dock down here. And I'm actually gonna go ahead and make this bigger, so make that take the full width, and then we can drag this guy into here, and then I'll drag the scene hierarchy to the bottom of that. Okay, cool. So you can see we have all of our sprite object gens. You can't change the name or anything right now just because of the way we have it. But yeah, they're there, and we also have one extra one. So there's a phantom object or two somewhere in here, because we have 6 objects up here, but that's more than 6. So yeah, but if you drag a new one in, if I click this, you notice that as soon as I clicked it, we got a new sprite object in there. So it's working properly. That is cool. We have the beginning of our scene hierarchy panel. Like I said, we're working towards what I showed you in the beginning of this video, what I have in Cocoa Engine, which was only 500 lines of code, but let me tell you, that was the most painful 500 lines of code I've written in a while, okay? There's so many edge cases and everything when you're dragging these things around and rechilding, reparenting, and I think I still have another bug. I think I saw one while I was demonstrating it to you guys, but yeah, we'll be working towards that, and hopefully we'll get that done within the next few episodes. In this episode, we will be continuing our journey with the scene hierarchy panel, which is this thing right here. Specifically, we will be creating this functionality to rename objects. So you can see this is called sprite object gen, but if I change it here, I can change it to game object. And you can see it also changes dynamically down here as well. And if we go ahead and change another object's name here, you can see that it changes in the scene hierarchy panel. We will also start to implement our drag drop functionality. So I can pick up this object, then I'm dragging around this little phantom object here. And then you can see if I highlight over any of these objects, it highlights yellow unless I'm highlighting over the object I started from. Then we can drop this into a new object and we'll get a notification that we had a payload dropped. So we'll be looking at how to do all of this in today's episode. Before we start coding, let's take a look at the way drag and drop works in ImGui. Drag and drop in ImGui is actually pretty simple to wrap your mind around. I wanted to go over it real quickly just so that there's no confusion whatsoever about how this works though. So the way drag and drop works in ImGui is you have these payload objects, and these payload objects consist of a type and the object that your payload is. So say the user starts dragging an object. What do we know? Well, we know the user can only ever be dragging a single object, or maybe like a collection of objects, but they can only be dragging one thing at any given time, right? Because the user only has one mouse. So ImGui gives us this global context, which is the payload. And we can use this global context anywhere in our code. So we can say ImGui begin drag drop payload, and while the user is dragging that object, we set whatever the payload is, and it will stay this payload and persist over several frames, which is actually kind of uncommon in ImGui since most of data is dynamic and not persisted over several frames. But then we can also accept that payload, and as long as it has the same type, we can accept that object. Now, what is the type? The type is not the object's type. So if this was a game object, we're not saying accept anything of game object type. The type is just a string, and the string is set by the user. And what you want to set it to is something unique, because you basically want to have, for every drag, you have a drop. And so for every drag source, we want to have a unique type that corresponds to the same drag source. So we'll be calling our type something like scene hierarchy. And I've been spelling hierarchy wrong too, so I'm going to try and fix that in this video. But basically that means that any drop source will accept anything with the type of scene hierarchy, which was set by this drag source. And anything else will not accept this. So it's pretty simple. I mean, it's straightforward, what you would expect. Another thing to note is you can only type in up to 32 characters in this type. This is not a limitation in ImGui if you're writing in C++, but it is a limitation of the library we're using in Java. And I'm not really sure why this was chosen, because I exceeded it very quickly when I tried to create a type of more than 32 characters. Anyways, though, let's go ahead and see how this works in the actual code. I'm back in the code right where we left it, which was refactoring it a little bit. And I'm going to mention something before we start real quick. Notice how I have the docking, and also if I minimize this, I have the viewports enabled. So all the code that I had was correct. The one thing that I had was wrong, which thank you to the person who pointed this out. I can't remember your username right now, but it's in the comments if you want to see who pointed that out in the last episode. Inside of ImGui layer, basically when we were setting the input flags, the only thing we had to do was say add config flags, not set, because if we set, we're setting it to 1, whereas we really want to add 2. And yeah, this is a little bit different because inside the actual ImGui code, you would basically say something like io.flags equals or equals, and then put your flag there, which I kind of like, and you can't really do that in the Java syntax. But anyways, just change this to add config flags, uncomment the code we had, and you should have docking and viewports enabled and working fine. Now, let's get into what we need to do to make this code work. The first thing we're going to need, because I'm going to work on having that name pop up so you can edit the game object's name, we're going to need to put that in somewhere. And I like putting it in the transform just because I do think it makes sense. Like Unity's code has the name of the game object in here, and I think that does kind of make sense in this case too. And so we're basically just going to go ahead and say right in here, gameObject.name equals, and then we're going to create a control called JImGui.inputText. Label is going to say name, and then we're going to pass in the gameObject.name. And we have to do it this way because we are assigning it, and we can't just pass by reference like we did here, because it just doesn't work with strings as well as I would like. Anyways, let's go ahead and go into JImGui and create that input control. So inside of JImGui, I'm going to scroll down to the bottom, and let's just go ahead and copy this, and we'll use this as sort of our base. First of all, we're going to change this to a string, and then we're going to change this to, say, input text, and we are going to take in a label, and this will say string text. So this will just be whatever text is in there currently. We're not going to need this result, and we should be able to just push the label as the ID as well. That should be fine, and this should all be fine too. That will just say name. Then right here, what we're going to do is say I am string out string. So this is sort of how we're going to edit it, is a new I am string text, so whatever they pass in, and then this is important, make sure you give it 256 as length. So this means that they can input game object names up to lengths of 256 characters. You may make that longer, you may not. It depends on what your needs are. It's really hard to find a good length for something like this, but you do need to input it because it is important that your engine's not allocating memory everywhere. And this is one of those things that ImGui does to ensure that we only ever have 256 buffer characters set aside, so 256 bytes. Anyways, we'll say if ImGui dot input text, and the label we're going to say is hashtag plus label, so that will hide the label so we don't see it. And then we're going to give it the out string, and that will basically just give us the ImGui label or editor for our text. So it's like a little text input editor. And then we can say ImGui.columns1. So if they did edit it, we just want to exit early, and then we'll say ImGui.popID, and then we'll say return out.get or outstring.get. So we're basically just doing this part, which makes sure we don't get a pop push error, and then we just return the new string. Otherwise, if the user didn't do anything, we'll do those pop in the columns again, and then we'll just say return text. So we'll return what they passed in. That way we're not creating a new string or anything. We're just using the same object, which should hopefully help out a little bit. Anyways, if we go back into transform now, you should see that that's fine. And if we go ahead and start up the engine, then click onto one of these objects and click it over here, I'm going to click the transform, and actually clicking it over here doesn't do anything. If I try and change this now to Gabe, you can see that it changes it up here as well. And if I go ahead and click onto a new object, this is kind of interesting. You'll notice that it automatically changes the name here. Now that's just because it's kind of a quirk of ImGui. Since we're using the same input text, it sort of copies over the data, which is undesirable. Now I haven't found a solution for this yet, but once I do, I'll update you guys with that solution. For now, if it changes it, if you don't want it to change it, you could change it here. If you click out and lose focus, then you click into a new object, you'll notice that it did not change the name. So that's just a quirk. You could do something like lose focus if they do change it, which could be annoying. So it's just very iffy on how you want to go about doing that to make sure it doesn't copy it over to the next one. Anyways, with that aside, that is the first part of what we were looking to do. Now let's go into the scene hierarchy window, and I'm actually going to rename this because I don't like having typos in my code. And I should have seen too, because IntelliJ even told me, look at this. It says typo in word hierarchy, and I just did not notice that. So we're going to go ahead and refactor this rename, and this should be IE, not EI. I guess this is just a quirk of English. I don't know. Anyways, with that spelled correctly and right here as well, we should be good to continue now. One of the things I'm going to do just to kind of consolidate our code is create a private Boolean do tree node. And this way we can have all of our tree node code in here. And then we're just going to copy all of this, paste it into here. Then we're going to go ahead and say tree node open equals do tree node. And we're actually going to have to pass it a couple of variables too. It says we need an index and we need a game object. So we'll just say pass in the game object, which we'll call obj, and pass in an index, which we'll call int index. Then we'll just pass those in over here. So we just pass in obj index, and we should be good. Cool. So this is functionally the same if we were to run this after we return the tree node. So if we were to run this, we won't get any changes. We've just refactored a little bit of code. It's going to move it over here for me just because that's what it does when you reset things like this. But it is the same code. Nothing's changed. Now what we're going to do is create the drag drop source payload. So how do we do that? Well, immediately after the thing that you want to become a drag drop payload, which in our case is the tree node, okay? So the tree node is this here, right? We want to click this, be able to drag it. That is the tree node. We want that to be our drag drop source. So immediately after we finish doing stuff with it, we say if ImGui.begin drag drop source, which says if the user clicks on it and begins dragging it. And then right after this, we'll say if, because we want this to be a source and we also want it to be a target. ImGui.begin drag drop target. So this says if they're hovering over it with a source in their hand already. So this basically does what we want it to do. Now, after we begin the drag drop source, we can never forget to ImGui end drag drop source. And likewise, we can never forget to end drag drop target. All right, now what do we do in the in-between part? Well, we basically want to say if they're starting to drag something, so we're in the source, we want to set the payload to whatever game object they just clicked on, right? Well, what object did they just click on? It's the object attached to this. So we can say ImGui.set drag drop payload. What type do we want it to be? I said we could just call it something like scene hierarchy. And then we want to set it as an object. So I'm going to say obj. So we want to set it as the game object. And the original ImGui code just looks like this, but we have an extra function in the Java version where we can say set drag drop payload object, and we set it to our game object there. Now, that's good. We set the object and everything. How do we get the text there? Well, the next thing you do, you can say imgui.text, okay? And I'll explain how this works in just a minute. And we're going to give it the name, and that should be it, okay? So we just set drag drop payload. We do this text thing, then we get this end drag drop source. Now, let's see how this works real quick, okay? So if we click onto one of these, we start dragging it, you'll notice it says sprite object gen. How do we get this hovering part, right? Why is it saying sprite object gen? Whatever you put in between these two lines of code, so in between set drag drop payload, in between end drag drop source, whatever ImGui code you put there, it will end up as the object. So we could also go ImGui dot, I don't know, button. And then we're going to say this is a button, okay? If we hit Shift F10, build and run this, and we drag, look at that. We've now got a text element and a button in there. So you could add as much stuff as you want. You could add images. You could add whatever the heck you want to add there. And it will sort of just set that to the payload, which is really cool because this allows you to enable cool features like dragging an image from a texture picker or, you know, anything else you want to do. We're just going to leave it as the text because I think that's descriptive enough for what we need. Now, inside ImGui begin drag drop target, how does this work? Well, we say object payload object, or I'm just going to say obj, equals ImGui.accept drag drop payload object. What type? We need to make sure it's the same type we put up there. So scene hierarchy. And this leads me to the next part, which if you look at the ImGui code and what he does in his examples, he actually does something like this, and I like this. we'll say private static string payload drag drop type equals, and I'm just going to do that, and then we'll delete the extra quotes so that we have those deleted. And then we're going to replace these. This way you can't make a typo, and if you ever refactor something, all you have to do is change the string in here, and then that will change everything. So this is definitely the best way to do something like this, and it just makes sure that we don't shoot ourselves in the foot with something stupid. Anyways, so we get the payload object, and we say if the payload object is not null, so this means they are dragging something. Well, we still have to check and see if it actually is a game object, because they could be dragging anything, right? Technically, it should, since we're accepting only objects that have been dragged with this type, it should be the object we're looking for, because this will not be null only if we have the correct type. But it's always good to check, and he has this in his code, so I'm assuming it's probably good to do this anyway. So we'll say if payload object.class is assignable from game object.class. So we know we definitely have a game object here. Then what we're going to do is say game object player game object equals game object payload object. And then we're going to say system.out.println payload accepted single quote plus player, this is just for testing real quick, dot name plus single quote. Let's see if we get what we expect. So now I should be able to drag these. If I go ahead and drag, you can see that it drags over this, and I don't think this is working properly, but let's drop it in here. See if we get any, nope, we did not get any messages. So I made a typo or something. And this actually brings me to a bug that I missed in the last video. So the reason we weren't getting the payload accepted is because all of our objects share the same ID currently. And the reason they share the same ID is because we're pushing index, which if we look at index, before I had it like this. So index was always 0, and I pointed this out in my last video in editing, but I never actually fixed it in the code. So if you just add in this line, index plus plus, then what you'll see when we run this is if you drag the object, and you can see that it highlights over the different objects. And if we drop it, we should see sprite object gen was accepted, and we get that right here. Now, why does this matter? If we don't have a unique ID here, a unique index or whatever, just anything, then ImGui is going to end up thinking that every single, because it associates with ID, it doesn't associate with anything else. And since we're explicitly setting the ID here, which we need to, because in the case of a tree node, it kind of expects it. So you could also change this to just object.name. I changed that for testing purposes, and it should work the same. Yep. But basically, this just ensures that it knows that each of those is a unique object, and you're not trying to drag it into itself. Because one of the other features of this drag drop payload is if you try and drag it into itself, you notice it doesn't get the yellow highlights, and that's because you can't drag an object into itself. It doesn't make sense, which is good. But let's just make sure this really works. We'll change this name to Gabe, and then we'll drag this into here. We should see that Gabe was accepted as a payload. Drop that. And if we look up here, we see payload accepted Gabe. Okay. Anyways, that is a very brief introduction to ImGui drag and drop payloads and all that stuff. It is interesting stuff. One of the things we're going to learn about right after in the next episode is about dragging into this window. Because right now, if we drag into this window, it can't accept anything as a payload, because it's not a drop target, okay? But that's important because what we want to be able to do is to drag things in between. So if we drag the mouse in between these two objects, we want to sort of say, hey, we're reordering here, which is a feature you'll notice in the Cocoa engine when I showed you that. And we'll talk about how to make all of those implementations in the next episode. Real quick, before I leave, I do want to say I'm sorry I haven't been releasing as often. It's just really hard to come by time right now, and it's really hard to come by motivation to be working on the practice engine, my normal engine, and then my full-time job. So I'm trying to continue to release weekly. Hopefully I will be able to keep that pace up, and hopefully the videos continue to come. And I don't want to lower the quality, which is another reason why I haven't been releasing as much. So I hope you guys can be patient with me as I try and get through this time. And hopefully the videos will start to come a little bit more regularly in the near future. Now, real quick, before we start this episode, I have to talk about a couple things. First of all, I plan on ending this series very soon. However, due to popular request, I have decided to finish the series off to a point that I think is acceptable. At the beginning of the series, I said you would be able to build Mario with this game engine. We're not at that point yet. So we will finish Mario, and then once we have Mario finished, I'm going to end this series in favor of the C++ series and shifting the channel towards a more C++ mindset. So keep in mind, this code is not going to be my best code. The way I would write an engine has changed pretty drastically within the past few months just because of me working on one in C++. However, I can't really translate the C++ into Java because we don't have access to some lower level features that I'd like to use. So for instance, with the scene hierarchy panel, we really won't be able to finish that. So I'm going to sort of streamline the process of finishing this engine. We will finish animations in the next couple episodes, then we'll add sound in the next couple episodes, and then we'll build Mario using what we have, and we will conclude the series. So towards the next couple episodes, what we're going to be working towards is this. All right, you can see that I've got Mario. We have this question block that's blinking and everything. Everything's working good except for the gizmos, which we'll fix in another episode, okay? You can also see that when we bring in an object, it's highlighted differently. The mouse coordinates are working perfectly. So before I had some issues with the way I was calculating the mouse coordinates in world space and vice versa. So that has been fixed. You can drag and drop multiple objects into the scene. No box select or anything like that. And you can see that sometimes we get duplicates, but I expect you guys to be able to add those features at your leisure after the engine concludes. So this is what we will be working towards in the next couple of episodes. This episode is all about bug fixing. So we're going to fix up the mouse coordinates and several other things that were not working correctly. So in the last episode, we left off with something like this, where we just sort of had some blocks sitting on the screen that kind of moved around like this and stuff. I'm just going to go ahead and delete all this because we will be doing a lot of new stuff, and I don't think it's helpful to have those there right now. Anyways, if I play and stop this, you can see that we've got everything just the way it was working before. And I'm not going to go about solving these bugs in any specific order. I am going to start with the mouse listener because that was one of the biggest bugs. So if we go into our mouse listener class, we can see exactly what the problem is. What I'm going to do to show you sort of how I solve this, because you do need to know how to solve this and everything in order to solve this in the future yourself if you ever want to. First of all, let's remove a bunch of unnecessary junk that is in here. So I'm just going to remove this. I'm going to remove this. We'll keep scroll X. I'm going to get rid of the world DX and DY because we're going to be sort of replacing those with something a little bit better. Screen X, screen Y, I'm just going to, well, I'll leave it for now so that we can see what the problem is and how I was able to spot the problem. But yeah, then I'm going to get rid of this ortho X. Going to get rid of this ortho Y function. Going to get rid of, okay, yeah, so that's all fine. And then I think there might be one more. Nope, that looks good. So then let's just remove these unused variables up here now. And that should be good. So now if we try to run this, we're going to have some problems. And also we will have to remove all of this stuff and all of that stuff. So if we remove all that, hit Shift F10, it's going to say we can't find a bunch of symbols. So we're going to replace this stuff with just temporary placeholders for now. We'll just say get X. Well, we'll do get screen X because we're going to replace that one with a different function too. So this way we can find all these functions again. So we'll replace this just so that we can get it compiling and see what the problem is. And then if we go ahead and in gizmo.java, it looks like we also have some errors. Replace this with screen X and screen Y. In mouse controls, we have some errors, so just replace these two as well, screen X and screen Y. And then in scale gizmo, we also have errors. Once again, screen X, screen Y, translate, same thing. Mouse listener, same thing. Okay, so we have all this stuff, we can get rid of that. Now, if we run this again, we shouldn't get any errors. Oh, we got an error, I missed a couple. Replace that, replace that. Okay, so now we run this, we don't get any errors, that's good. Now, nothing's gonna work, right? Because we just sort of replace these with junk, but it works. So next thing I'm gonna do is Control-Shift-N, go into Level Editor, Scene Initializer. And then I'm gonna go ahead and go into this ImGui function, just so that we have a place where we can print stuff out. And I'm gonna print X plus, and then we'll say screen coordinates or mouse listener, sorry, dot get screen X, and duplicate that line, and then we will also do Y. and you will see exactly what the problem is here. So now let's go into mouse listener, and we'll take a look at what the problem is. So if we look at calc ortho x, and we put in system.out.println right here, current x. Let's take a look. What is this supposed to do? This is supposed to return 0 to 1 if the mouse is over the left side of the game viewport and the right side. Let's see what happens now. So if I hover the mouse over here and then hit Alt F4 to exit, we're getting 0, so that's not bad. But then if we go over here, hover over here, hit Alt F4, yeah, this, oh, okay, so we didn't normalize it. I was like, this is completely wrong. Okay, go down one more line and then put this, and what I'm gonna do is instead of, so this is supposed to turn it from a range of -1 to 1, right? So this gets it from 0 to the game viewport size .x, and then this will get it from -1 to 1. So if we go to the right side of the screen, we should get +1, which we get, so that's good. Then if we go to the left side of the screen, we should get -1, which if we look at this, we also get. So that's good. Where's our problem then? That's returning the values correctly, right? Basically, I believe that since we're multiplying like this, we're actually modifying these variables. So what I thought would happen is if we're doing multiply, it would put the result in view projection and not modify any of these variables. Well, that's not actually true. It's modifying everything. And so this is just completely screwing up because every time you call calc ortho x, it gets a new value inside of here, and then it's just modifying state left and right. So we basically just have a problem within here. Most of this is actually pretty good. I'm just gonna change the names of a few things, and then we're gonna reformat this a little bit. So instead of calling this calc ortho x, because I don't think it's not clear to me what that means, you know, we're going to call this something a little bit easier to understand. So we're going to make a function and call this get world, which will return a 2D coordinate in world coordinates from the mouse, right? This is the mouse listener. So get world is going to get the mouse listener's coordinates in world coordinates. So we're also going to need the current x. You can see that we have current y here, but we also need current x. So let's go ahead and copy this, which should be good. We'll paste it down here. Now we have current x and current y. The vector, I'm going to populate with both of these. The vector looks okay. We have x, y, 0, 1. You need to make sure that w is a 1, otherwise you will get errors. And this current y value looks okay too, to me. I might be wrong, but we'll revisit that if we need to. And then this is where I'm going to make like the real changes, right? So we have this view projection. I'm just going to get rid of that notion altogether. What we're going to do instead is we're just going to say matrix for f temp equals a new matrix for f, and we're going to use the camera dot get inverse view. Okay, and let's actually name this something a little bit better. Temp is a kind of stupid name. We'll name that inverse view. Then we're going to make a matrix for f. We'll call this inverse projection equals new matrix for f camera get inverse projection. Okay, so what we're doing here is we're basically ensuring we will not modify the camera's actual matrices because we're wrapping it, we're creating a completely new object. So this is good. This will make sure that we don't do something stupid again, or I don't do something stupid again. Okay, then we're just going to do all the multiplication right here. So we're going to say inverse view dot multiply inverse projection, and then we're going to multiply that by temp, which should translate this current x, current y into world coordinates. Then we're simply going to return new vector 2f temp.x, temp.y. Now let's go ahead and change the names of these to get world y, and instead of having all this duplicate code, we can just say return get world.y. And we need to return a float. We can't return void there. Then we'll do the same thing for this, except we'll call this get world x. And then right here, we will simply say return get world dot x. All right, so that should be good for the world coordinates, and screen coordinates actually look good to me. I will simplify things a little bit more. We'll just make a static vector 2f get screen and do something similar to what we did down there. So we'll copy that. We'll copy just this y portion right here. And then we will say return new vector 2f current x, current y, which is good. Then right here, we can just say return get screen dot x. And then right here, we can say return get screen dot x. This should be dot y, that should be dot x. And that will fix it for now. Real quick, I'm just going to change the names of these functions just so that we can get all those errors and correct them appropriately, okay? So inside of editor update in editor camera, when we are doing this, we do want the world coordinates, not screen coordinates. So we'll say get world. Actually, we could just say new vector f mouse listener.getWorld. Simplify this even more. And then we'll do the same thing here. This should be world coordinates, so we'll say get world. And actually, we don't even need to do this. We can just do this because we are returning a new vector out of the mouse listener already. All right, that should correct the editor camera. Then let's go into Gizmo. I believe this is also looking for world coordinates, so we will do the same thing here. We'll say mouse listener.getWorld, which should correct that. And then it looks like we have one more error in here inside of the gizmos. So we'll say mouse listener.getWorld, and we should be good there as well. Let's go on. We have the properties window. Okay, so this is where we actually want screen coordinates, right? Because inside the properties window, this is basically checking which pixel we're clicking on, right? Because we're picking the frame buffer texture. So we want screen coordinates, not world coordinates. So we will say mouse listener.getScreen X. So this will actually correct itself once we rename those functions. Mouse controls, let's go into here. We're going to want this in world coordinates. And we'll do get world X and get world Y. Oh, and it looks like we made those private inside the mouse listener. Or maybe you didn't, but I did. So let's go ahead and we will make these public, not private. So just rename those and we should be good. If we go back here, these errors disappear. Inside of scalegizmo.java, we will change this to get world X. Most of these are just going to be world coordinates, but it's good to double check all of them just in case, like that one we had where we wanted screen coordinates. Once again, world X here inside of translategizmo.java. And then lastly, inside of mouse listener, we will go ahead and remove those. Okay. And then let's go ahead and also change the name of our screen coordinates back to get screen X and screen Y. Then if we run this, we should get no problems. We get no problems. Right now, the object is not clamping to the right place, right? And why is that? Well, if you remember, we changed our code so that it centers around the origin of the object, not from the bottom left corner anymore. So it's kind of just placing it in the wrong position. So this is actually pretty easy to fix. If we just go into our mouse controls, I believe, we'll be changing quite a bit of code here. We'll take it one step at a time though. So we want to get that to the correct place. Right now it is kind of off kilter. So we can just add in half the grid width and half the grid height to wherever the object is, and that should correct part of this. So if we just go ahead and wrap this, we'll do a parenthesis here, go to the end of the line, parenthesis here, and then we'll say plus settings dot grid width over 2. Then we will do something similar for the height. So this will basically just make sure that we are in the correct square. We're not like halfway between two squares, right? So if we do that and then go back into here, we should see that it should be in one square, which it is, almost. So looks like the Y position is off. We will explore why that is. I think I might know, but we'll check it out. Oh, it's because I forgot to do over 2. So that was very simple. Now we go back into here, and then if we drag, okay, yeah, we drag and it is in the right place, except it's 1 off in the X, right? It's 1 to the right. So what we can do to fix that is, instead of doing anything, this should be math.floor. If this isn't math.floor, then we won't be rounding consistently and we'll actually end up changing. So if we're on the left side of 0, then this will do one thing. And if we're on the right side of 0, it'll do a different thing. So if we change that to floor, we should fix, yep, the X coordinates are now in the right place. And the Y coordinates are not. If you notice, it's like halfway between it. And why is that? Well, there's something weird going on, right? Let's go ahead and just first of all, check one thing, right? If we go ahead and print out mouse listener.get world Y, and I'm showing you this because this is sort of how I debugged, right? And if we go into our scene, just to make sure we know where the camera is located in the world, let's reposition the scene to 0, 0. So the bottom should be 0, the left side of our screen should be 0. And if we put our cursor right at the bottom there, we should see 0. So let's just make sure that is true. Well, we'll see 0 if I think we're holding an object. Yeah, so let's move this out of here actually, just so that we can try and see what's going on. So we'll put that right there. Then if we hold our cursor right at the bottom of the screen, we get 0.0. So that's good. We are hitting the right location there. If we hold it at the top of the screen, we should get 3 because our projection size is 3. Yep, we get 3. That's good. Okay, well, what's the next thing we could check? Well, we should check this line right here. This should be at 0.25 because that's the settings I have for my grid width and grid height. Well, what is this? What? This is 0.32. That's not right. Okay. And why is that not right? Well, it took me quite a while to figure this out, and I think I finally solved it. It's something inside of not ImGui layer, but our game view window, right? Because we're using this to sort of figure out where certain coordinates should be and everything. Now, I made a lot of changes in here, so we're just going to go through and make all of the same changes, and hopefully it will fix our problem. So first of all, what I end up doing is I don't do this first. Instead, first I set the cursor position to ImGui.get cursor pose X, ImGui.get cursor pose Y. And technically, this does nothing. So if we finish this, we should be able to remove this line and it should function exactly the same, hopefully. If it doesn't, then something's weird. Okay. Then we do this whole window size and window pose and everything. And then we're going to go ahead and do ImGui.set cursor pose, window pose.x, window pose.y. And let's go into get largest size for viewport. The changes I made in here was I just removed the scrolling. We shouldn't have to worry about scrolling because we're setting the size of the contents explicitly and we're only setting it to the maximum available size. So we can remove the scrolling safely and not worry about that. We'll do the same thing down here for get centered position for viewport. So we'll just scroll down, remove that as well. Then inside of this position right here, I had to add 10 to the X coordinates to get it to actually work right. Not sure why. Let's also remove the scroll from here. We don't really need that. And we're also going to remove this whole top left thing. And instead of setting the left X, bottom Y, all that to that variable, we're just going to set it to window pose, right? Because that is what it should be. So if we just do all this and then add 10 here as well, to correct for that offset that I'm not sure why I'm getting, but 10 seems to be the magic number. If it doesn't work on your resolution, then maybe this is some ImGui setting that we need to figure out. Then inside of here, we're just going to set it to window pose.x plus 10 and window size.x, window size.y should be good. Let's go ahead and run this and see if this fixes it. I honestly can't remember what change I made that fixed this. So, okay, yeah, you see it's working now. Our Y coordinates are in the right place and it's working. So I'm not sure which one of those changes specifically fixed that bug, but one of them did. It was weird because I was thrown off because I was just checking the bottom and the top. And I was like, oh, those work. So of course everything in the middle is going to work, but you know, it's not. So yeah. Anyways, that is that corrected. Let's go ahead and implement that dragging feature. You can see that something weird there just happened because that did not work right. So let's go ahead. Stop printing out this value wherever we're printing that out. So inside of mouse controls, we'll just remove that print line and then we're going to do some more stuff in here. So first thing we're going to do is we're going to add a debounce time in here. So right now, if you click, you could place multiple objects on accident. We don't want to do that. So we'll go ahead. Technically you can't because it'll automatically just click onto the object, but we're going to fix that too. We'll go ahead and add a private float debounce time and we'll set that to 0.05f. And then we're going to say private float debounce equals debounce time. So this will be sort of like our reset value, right? Then we're going to go here and we'll say if holding object is not null and debounce is less than or equal to 0. And we'll just subtract dt from debounce right here. This way we just can hold and click without worrying about placing multiple objects too much. We'll just say debounce equals debounce time in here. And then I'm going to add in one more key combo that's kind of useful. If mouse listener dot mouse button down, GLFW escape. Then we're going to go ahead and say holding object dot destroy. And we're going to say holding object equals null. So this way we just destroy the object and it is no longer holding it. So if we go back, we should see that if we're holding an object and then you hit escape, and the problem is I did mouse button down. Escape is not a mouse button, it's a key button. So let's do key listener is key pressed. Redo this and we should get the correct value this time. So if we hit escape, you can see that the object destroys and it's kind of out of sight, out of mind. Now I'm going to modify our place function just a little bit. It's going to do a little bit more than just placing the object by setting it to null. That way we can hold down and place multiple objects. So what we'll do is we'll say game object, new obj equals this dot holding object dot copy. So we'll copy the object that we're holding. Then we'll say new object dot get component sprite render dot class dot set color new vector for f1111. And the reason we're doing this is because we are going to set the transparency to a little bit lower color when we pick up an object in just a minute. So we'll do that. And that means we will have to reset the color here. So this is basically just setting the color of whatever object we just copied to white. And then we can go ahead and say window.getScene.add game object to scene, new obj, which should add the object to the scene. Now, if we go ahead and run this, you can see that we can click and drag, and it works like you would expect. Then if you hit escape, it removes it, but you will notice that if you delete some of these, they were placed down multiple times. And you can mess around with the debounce time and adjust it to something that you like, just to make sure you don't place down too many copies. Let's go ahead and make it transparent when you're holding it so you know that you're holding an object. So right here, we'll say this dot holding object after we set it, dot get component, sprite render dot class dot set color, and we'll just say new vector for f 0.8, 0.8, 0.8, 0.8. So we'll just set it to a white color with some transparency just to make it a little bit see-through and easier to tell that that is what we're holding. And let's actually set this to 0.5. Then we're going to go ahead and say this dot holding object dot add component new non-pickable. That way we don't click on it, because right now what will happen is if we place an object, so you can see that it's transparent first of all. Then if we place it, you can see that immediately we select it, and notice that we're selecting the object we're holding, right? So if I click, we're not selecting the object we just placed, we're selecting the object that's like in the mouse cursor, and that's really annoying. We don't want to do that. So if we just make sure to add the non-pickable class, that will make sure that you can't actually click on that object. And if we add it again, you'll see that we don't get that annoying glitch. And then we can go ahead and just click and drag. You'll notice our scene hierarchy window over here just adds a ton of them, and they all get added to the scene. We just want to make sure that we also remove the non-pickable component once we finish with this. So we'll say new object. So after we copy it, we'll just remove the non-pickable class. That way you can once again select it once it's actually in the scene, right? So now we should be able to click, then we can select them and we can do what we want with them. The gizmos are messed up. We'll work on that in the future. One last bug that we're going to fix in here real quick is if you notice, if we click down here, we're holding this object. Then if we click down here, we select a new object. But what just happened? Well, we accidentally placed this object, and it's a ghost object because it's not really added to the scene. You can't click on it. You can't delete it. It's horrible and annoying. So let's fix that. We can just go up here, and then when we pick up the object, we'll say if this dot holding object is not null, this dot holding object dot destroy. Very simple. That will make sure that if we're holding an object like we are right now, and then we click a different object, we can start placing this object, and we don't place a duplicate somewhere that we don't want to. So that solves that problem very easily. Now let's go to the properties window and add one line of code that will make our lives a lot nicer too. So right now, if we were to pick up an object, start dragging and placing, you'll notice that we can start selecting objects. You can see the gizmos pop up real quick and then throw the object way down. That's annoying. We don't want to do that. So in the properties window, this is where we basically check and see if we're clicking on an object. We can simply just say if not mouse listener dot is dragging and all that other stuff. That way, if we're dragging the mouse, we won't end up selecting an object, right? And now we can place objects and it doesn't select them till we actually click on them. That is also very nice, right? Now we can place a lot of objects and not have to worry about it getting sort of stuck in the scene. Real quickly, let's just go into sprite render because there was some code that I've had in here for a while. I'm just going to remove that because there's no sense in having it. I'm going to make this a little bit easier to read. And also this says color pickier. This should be a color picker, so I'll fix that real quick. Don't know if you had the same mistake or not. Okay, and I think that is it for this episode. We just fixed up some bugs, made the workflow a little bit nicer. Now you can add multiple objects, which is nice, and then just sort of fill in the gaps here. Afterwards, the only downside is you do get duplicate objects. You could find a workaround for this, but I'm not going to spend the time to do that because, as I said, I just want to get to this to a point where we can build Mario, and then I'm going to finish this series up. But I hope you guys enjoyed this. If you did, please hit like and subscribe. And stay tuned for the next episode where we will be implementing these animations, right? I also didn't show you. If you click on the animations, you can click the state machine up here. You can change individual frame times and the title of this animation state. So right now, Mario only has one state, which is run, but we could add a jump state, a swim state, anything else, and then triggers to trigger him from one to the other. So we'll talk about all that. But if I move this up, you'll notice that he lags on the first frame, and then the next 2 frames go a little bit faster. And then if I move this to like 0.1, then you'll notice that the first frame goes very quickly. So that's interesting, and it's useful because for this question block, we actually do want that, right? We want the first frame to last a little bit longer, and then the next 2 frames to be a little bit slower. So we'll talk about all that in the next episode. In this episode, we are going to be implementing animations, so we can actually have animations on the screen and Mario running around like this. Well, he's not actually running yet, but we'll add a character controller and all that good stuff in due time. Okay, so let's go ahead and work on this. Before we start coding, let's take a look at some drawing and see how all this works. So the type of animation we're going to be doing, first of all, is sprite-based, right? So we're not going to be doing any bone-based animations where you could like pick up an individual arm of your character and move that up and down. That's just too complicated, and I have not done that in the past, so I don't want to give a tutorial over something that I haven't done. We're just going to be doing sprites, so basically you have a sprite sheet where you have your character in multiple different phases. Maybe he's killing somebody or whatever, you know, and then you just play through these. Maybe this one's 0.1 seconds, this one's 0.2, then this one's 0.1. So it gives you a little bit of a lag for each time the frame, and we just sort of step through each sprite. This is definitely suitable for a wide variety of cases, and it is still used in a lot of different games. So we're doing sprite-based animation, and how are we going to implement the animation? Well, we're going to use something called a state machine, which I went over in an animation episode a while back, but it's similar to the way Unity does its animations, where basically we have a bunch of different states. So say we have an idle state for the character, we have a run state for the character, and we say on the trigger run, go from idle to run, and on the trigger stop, go from run to idle. The good thing about this is, say you also have a jump state, right? Or maybe not a jump state, but let's say you have an attack state, okay? And on this attack state, you don't want to go from run to attack. If you go to attack, you need to be in idle position. So you could basically say, well, run only goes to idle. So we can only go base here. So then if we attack, then we have to go here. Then we have to go to the attack state with this trigger. This is basically just a way to keep it so that your animations don't go in an incorrect order, right? And your animation state will always be in one of these states, which is good because you'll know exactly how it's going to switch from different animations to different animations, okay? Inside of, so the way we're going to code this too is basically this is just going to be an animation state class in Java. And this animation state class is going to have a list of states. Well, it's going to have a list of sprites, which basically are the different animations. And this sprite will also have a time attached to it to tell you how long to put that sprite on the screen. And then we'll have a bigger thing, which is like the run animation state with all its triggers. And we'll call that a state machine. And the state machine is basically this whole thing. It just has a list of animation states, which are each of these, and then a list of triggers. And a trigger is a string which goes from one animation state to another. Okay. And we can also, on side of each individual animation, determine whether it's looping and a few other things that I can't remember off the top of my head. Okay. So let's go ahead and implement this and see how it works in code. So like I said before, let's go ahead and simply add our animation state to our components class or components package. Now, this is not actually going to be a component, but
We'll put it here because that's just sort of where it makes sense to me. Now inside of this class, like I said, we're going to have first of all a string, which is the title of the animation. So like run, idle, whatever you want to call it. Then we'll have a public list of something we're going to call frames, which is just a sprite with a time. And we'll call this animation frames equals a new array list. And we'll create that object in just a minute. Then we'll have a private static sprite. Call this the default sprite equals a new sprite, which will return if none of the frames work that way. We don't actually break. It just sort of shows a pink pixel or something. I don't know. We'll figure it out. And then we're going to have private float. And let's call this time tracker. So this will basically be tracking the time that we're on a single frame and switch it from frame to frame as needed. Private, we'll have a private transient int current sprite. So this will be whichever sprite we are currently on. And we'll initialize that to 0. Let's also make time tracker transient because it really doesn't matter and we don't need to save that out. And then we'll have a private boolean does loop, which will determine whether this animation loops or not. Let's go ahead and add that frame class real quick before I forget. So let's just go in here, create a class called frame. This is very simple. It's just going to take in public sprite and we're going to have a public float frame time, how long this should last. We'll have a default constructor. That way you can serialize, okay. And then we'll have a constructor that takes in a sprite and a time. And then we'll just say this dot sprite equals sprite, this dot time, frame time equals time. And if we go back into animation state, we should see that this is all good. Let's alt enter and import this. We're now completely good. Now, the way I like to code this, let's also add array list real quick before I forget that. The way I like to code stuff like this is I like to code the functions first to see how I'm going to actually build it, because the best way in my mind to do this is like I want to see how I'm going to use it, right? So in my mind, I thought it would be good to have something called add frame, and this takes in a sprite and it takes in a frame time. So this will add one individual frame, and then we can literally just say animation frames.add new frame sprite frame time. That is very simple, and it is simple to use as well, which is good. Then we'll have a public void set loop boolean does loop. So this way we can set it to loop or not. So we'll say this does loop equals does loop. And then we have an update function, right? This update function will basically switch it from frame to frame for us without us having to know about how it's working or what it's doing or anything, right? So what we'll do is we'll say if current sprite is less than animation frames dot size, which will basically make sure that we're not going to get index out of bounds error, right? We don't want to do that. We'll say time tracker minus equals dt. So we subtract the time. And we'll say if time tracker is less than or equal to 0, well, then it's time to move on to the next frame, right? So if we're on frame 0, we need to go to frame 1. If we're on frame 1, we need to go to frame 2, so on and so forth. Then we'll say if we do not have the current sprite, so whichever index is not equal to animation frames dot size minus 1. So if we're not on the last frame of the animation and it doesn't loop. So if we're on any frame before the last animation and it's not looping, if this is not true, so basically this is saying if we need to move to the next frame, then move to the next frame. That's all that says. So let's say current sprite equals current sprite plus 1 mod animation frames dot size. This should work for looping animations and animations that want to stop at the end. Then we can say time tracker equals animation frames dot get current sprite, so whichever one we're on, dot frame time. And this will ensure that we loop for the appropriate times for each one, and we continue to loop through. Last thing we're going to want is a public sprite get current sprite, which will return whichever sprite we're on. We'll say if current sprite is less than animation frames dot size, then we'll just return animation frames dot get current sprite dot sprite. Otherwise, we'll just return that default sprite we initialized up there. And let's go ahead and make this default sprite something a little bit more flashy so that we actually know what this is. So we'll say public animation state, create a default constructor, and then we'll just say default sprite dot. Well, looks like we can't really do that. So, I mean, I guess you could get a custom texture and then set this to like a pink texture or something, just so that you know that there's an error and it's really obvious. This will just return a white sprite for now, which is fine with me, honestly. So this should do everything we need to do inside of animation state. Almost everything. We'll see a bug in the future, and then I'll talk about how I fixed it. Now we need our state machine, which is going to be a component, and it's going to be a little bit more complex. So we'll say create a new class, call it state machine. And the first thing I'm going to do is create a private class in here. If this was C++, I would just create a struct inside of the implementation file, but this is sort of the Java way to do that. So this is just a class that only state machine cares about, which is why I'm making it a private class in here. This will take in a private string, trigger. So this is the trigger, and then a public string state. And I'm actually going to move that up. Then we'll create a default constructor that does nothing. And then we'll create a constructor that takes in a string state and a string trigger. Okay. And then we'll just say this dot state equals state, this dot trigger equals trigger. This is just going to be a helper class for us. It doesn't need to be very fancy. We will need to override equals. So we'll say public boolean equals object O. And this is nothing fancy as well. We'll just say if o.getClass does not equal state trigger dot class, return false. And then we'll say state trigger t2 equals o state trigger o. So we'll cast it once we know that it is the same object, and then we'll just say return t2 dot trigger dot equals this dot trigger, and t2 dot state dot equals this dot state. All right. And then we also need to override our hash function because we will be putting these inside a hash map. So we'll just say public int hash code, and we'll just return objects.hash trigger state, and import objects by hitting Alt-4 or Alt-Enter. And this should say hash, not has. There we go. And then that should hash it for us, and we don't really have to worry about that anymore. Next, we'll say, what do we need inside of this state machine? We basically need a list of triggers, right? So we'll create a hash map, which takes a state trigger, and it returns a string. So it'll be like, basically, you have a trigger, and on that trigger, I want to go to this state, right? So when you're on this state and you hit this trigger, go to the state that this title says. And we'll just call this state transfers equals a new hash map. We're also going to have a private list of animation state, which is going to be our states, and I'll just make that a new array list. And then we're going to have a private transient animation state, which is the current state, and we'll initialize that to be null. And we'll have a private string, the default state title, which we'll initialize to empty string. So basically, this is the default state that we want to end up in, animation state. And then this is the current state that we are in, which is null because we don't have one yet. So once again, I like to code to implementation. And the way I would do this is I would say public void add state animation state. And this can literally just say this dot states dot add state. Okay, so we add a new animation state. That's simple, nothing too fancy there. What if we want to add a state transfer though? Trigger, transfer, whatever, you know what I mean. So we can say void add state trigger. This takes in a string from string to string on trigger. Okay, so this will basically say go from this state to that state on this trigger. And this is simple too. We can just say this dot state transfers dot put a new state trigger from to, or I'm sorry, from, and this is on trigger, and then to. So we put in our hash map. This is the trigger. So it goes from this state on this trigger to, and then we just give it whatever the state title is. So we get a state trigger, and then it returns the state we need to go to next. Lots of states, I know. Using this, we can actually build up our trigger function, right? So we can say void trigger string trigger. So you can call this function, which will trigger the next animation, whatever trigger your is. So we can say for each state trigger that we have inside of our state transfers key set, we can say if the state, so the state's title equals the current state's title, and the state's trigger equals dot equals the trigger that was passed in. This basically means we are on the state and it has a trigger equal to the trigger they passed in. So we know where we need to go. We can say if state transfers dot get state does not equal null. Then we'll say int new state index, and they can add in a null transfer, which basically means it goes nowhere. Then we'll say new index equals states dot index of state transfers dot get state. And I'm just realizing that this isn't actually gonna work quite the way we want it to. So we'll say int new state index equals -1. Then what we're gonna do is we're gonna say for int, or we'll say for state animation state s in states. Okay, we're getting wild here. We'll say if s.title dot equals state transfers dot get state. So basically, if we have the animation that this needs to transfer to, then we'll say new state index equals index, and we'll just say int index equals 0 right there, and then we'll just do an index ++ here, and then we'll just break out of this loop, which means we should be good. Then we can say if new state index is greater than -1, current state equals states.get new state index. All right, so this is a little bit complicated and convoluted, but it will basically just transfer us to the correct state depending on the trigger. If it has it, and it will do nothing if it doesn't. And if we get through this loop and we don't find one, we should say system.out.println unable to find trigger plus trigger. And that way we know something went wrong and we don't blindly go on. And we'll just return if we find something. So we can return out of this guy right here, which should be good. And I think that is, if we click onto this bracket, that's this bracket right here. So we can return right here. And that should do everything we want it to do. Okay, and then I'm gonna go ahead and override our start method since this is a component. I believe it's a component. We did not extend component, which we should. So we'll say this extends component. Should be good. And then right in here, we'll just say for animation state in states, if state.title.equals default state title, then we'll say current state equals state break. So every time we start the scene, we'll switch to the default state, which is good. Then we'll say at override public void update float dt. And inside of here, we can say if current state is not null. Then we want to update it. And then we also want to make sure that we set the sprite to the appropriate sprite that we need, right? So we'll just say sprite equals GameObject.getComponent sprite render.class. If sprite's not null, then we'll say sprite.setSprite current state.get current sprite. Cool, autocomplete did that for me. And then we'll go ahead and copy this, paste it, editor, update down here, just so that we get this updating in the editor. And when we play the scene, if you don't want it to update while you just have the editor running, you could just remove this loop and that should be fine. Okay, last thing we need to do is just make an ImGui function. That way we can actually modify this code. So we'll say for animation state in states, we'll just say ImString title. So you can change the title if you want. New ImString state.title. Let's go ahead and import that as well. And then we'll say ImGui.inputText state, and then we'll do a colon and we'll just say state.title. Then we'll say state.title equals title.get, right? So we just have a text box there that says title, and then we'll say index equals 0 because we're about to loop through a few different things. And let's actually set index to 0 up here, which should be a little bit better. That way we give things a unique ID. We'll say for frame inside of state.animation frames, we want to list each of the numbers so that they can change them if they want. So we'll say float temp equals new float 1, temp 0 equals frame.frameTime, ImGui.drag float. We'll call this frame plus index so that they know which frame this corresponds to. And then we'll just do a time so that they know this is the frame time. Then we'll give it temp and we'll say 0.01f, which was good for me. Change this to title too. Shouldn't be state.title, it should just be title. Then we'll say frame.frameTime equals temp 0. And we can say index ++. Okay, that should be good for that. And then lastly, we'll put a checkbox up here too to check off whether it loops or not. So we'll say ImGui.checkbox does loop. And then we'll do a space there just in case. And then we'll say state.doesLoop. Or we'll actually just make an IM Boolean. And we'll say does loop equals state.doesLoop. We'll make that public too, just so that we can see that in a second. And then we'll import that. Then we'll just say does loop. And then we'll just say state.setLoop does loop, which should be good. And we just want to make sure that we get that value. Okay, there we go. And then let's go ahead and make this public just so that we can access that, because I really don't care about private public things that much anymore. So that should be good. We just need to make sure we do no IM Boolean. And now we have an ImGui function that should let us alter different things. Now we need a way to get animations into the scene. Well, if you look at the GitHub repository linked in the description, you can find all these sprites and images there. And I have two sprite sheets, one cleverly called sprite sheet and another one cleverly called items. Okay, very descriptive. Those are sprite sheets that we will be using. And I am going to go ahead and go into level editor scene so that we can actually start adding some things, right? So first of all, what I want to do is I basically want to have a bunch of different tabs down here in this bottom window. So we have like this, and then we have prefabs, whatever else we want. So let's call this blocks instead of window. And then we'll say if ImGui.begin tab bar, and we'll just call this window tab bar. Wrap everything in here in that tab bar. Then we'll say if ImGui.begin tab item, and we'll call this blocks as well. Then we'll just wrap everything in that. So if we're on the blocks tab, we'll just leave this sort of the default, and then we'll make sure to ImGui.end tab item here, and also ImGui.end tab bar here. And then we'll say if ImGui.begin tab item, call this prefabs. Actually, let's call this, yeah, we'll call this prefabs. Okay. So this will sort of be like special objects that we create specifically for this. And then I'm going to do ImGui.end tab item right there. We'll put nothing in there for now just to make sure this is all working right. And then right here, I'm just going to call this objects instead of blocks, because that's a little bit more descriptive. First of all, it's going to mess up everything for me right now. So I'm going to do that, fixed up. Then I'm going to dock this back into here. All right, everything looks better again, except now we have some tabs. So we have blocks and we have prefabs, which is cool. So I'll exit out of that. Now inside of the prefabs bar, we basically just want to add some items very similarly to the way we did right here. So I'm going to copy that, paste it right here. Instead of getting this from sprites, I'm going to say sprite sheet player sprites equals asset pool dot get sprite sheet. And we'll call this assets/images/sprite sheet.png. Very clever name, right? And that should be the player sprites. Then we'll say instead of this is being sprites, we'll do this. This is player sprites.get sprite 0. Okay. We won't push any IDs because we shouldn't have to worry about that. So we should be good just doing this all as is. And then last thing I'm going to do is I'm going to change this to generate Mario, and we will create a function that does just that in just a minute. And everything else should be fine. Okay. And then I'm just going to do an ImGui.same line right there. Cool. So let's go into our prefabs and create a function, call this generate Mario. Let's copy this one as a reference, rename it to generate Mario, and remove all of that. Going to go back into level editor scene initializer. We will need the sprite sheet in here as well. So let's go get that again. Go back into prefabs. And then I'm going to go ahead, just paste that sprite sheet right there so that we have that available. Then we're going to call this Mario because this is what this will be. And we'll call that Mario up there too, just so that we know. And actually, let's call this, instead of creating the game object and everything like this, let's use the function we have right here. We'll say this is equal to generate sprite object. We'll give it player sprites dot get sprite 0. And then we'll give it a size of 0.25, 0.25, which should give us a base object to work with.
Let's make sure to return Mario here. And now we want to add an animation machine to this, right? So we'll code all this in. We'll say animation state run. So this is going to be our run state is a new animation state. And then I'm going to say run.title equals run. And then we'll say the default frame time is 0.23f, which is something that I thought looked okay. And then we'll add all the different frames. You could create a bulk add frame method if you want to, but it's easier this way since we do have to add frames individually. They're not really in line. So I'm going to get this first sprite that we have inside that sprite sheet. Then I'm going to get sprite number 2, which is at index 2, then 3, then 2. So it should just sort of loop back and forth. And then we'll set the looping to true so that this does loop. Then we'll create a state machine. We'll call this state machine equals a new state machine. And we can say state machine.add state run. So now we have the run state available to us in the state machine. We'll say state machine.set default state, which I'm not finding. So let's go into state machine real quick. I know we coded that. Oh, maybe we didn't. So we also want a way to set the default state, right? So let's go ahead and we'll say public void set default state string animation title. And we'll say for animation state in states if state.title.equals animation title, then default state title equals state. And then we'll just say if current state equals null. Then we'll say current state equals this state that we just hit, and then we'll break out of this. We can actually just return out of this. Otherwise, if we can't find one, we'll say system.out.println unable to set default state, or we'll say unable to find state plus animation title and set default state as a little note to ourselves. And this should be set to the animation title. There we go. All good. Let's go back into prefabs now. And now we can set default state to run, which is just run.title. And that should work for us. And now we will add this new state machine to Mario. So we'll say Mario.add component state machine, and he should have that. So if we hit Shift F10 and we hit prefabs, we get an error. Nice. So let's see what's going on here. Asset pool. We never added the sprite sheet, of course. Let's go into level editor, scene initializer real quickly. Scroll up to here. I am going to copy this guy right here because it is very similar to what we need. Paste it right here. Change this from sprite sheets to images / sprite sheet. We do the same thing right here. Change that to sprite sheet so it has the correct path. And everything is the same except this guy just has 26 sprites. Let's go ahead and copy this one more time for now because we did add 2. The second one is called items, and we'll just call this items. And this one is almost the same except it has 43 sprites in there. Okay, now if we hit Shift F10, we should be good. Fingers crossed. It's running. If we hit prefabs, we get Mario here. And then if we drag Mario in, you can see he's running. So then if we were to drop him, he's not showing up. But if we hit play, stop, he's still not showing up. He's there, he's just invisible. So what's going on there? Well, we basically have to make sure to refresh the texture ID because the texture ID sort of gets lost in translation as we're copying things and stuff. And in order to get around that, we can go into our animation state, or actually let's go into our state machine and we'll create a function up here that we'll just call public void refresh textures, which will basically just make sure that we actually have our textures showing. So we'll say for animation state in states, state.refresh textures. Then let's go into animation state and add that right here. So we'll just say public void refresh textures. And we'll say for frame in frames, frame.sprite.set texture, asset pool .get texture, frame.sprite.get texture, .get file path. Okay, so it's kind of convoluted, but we're basically, and I called this animation frames, not frames. We're basically just making sure to reset that texture ID reference so that it actually has a handle on that.
And now if we go ahead, first of all, when we're loading the scene, it's not working. So let's go ahead and fix that first while it's fresh in my mind. So if we go back into level editor, scene initializer, right here, we sort of did something similar for sprite renders, and we'll just add in another one for animation or state machines. And we'll just make sure this is state machine, call it state machine. And we will simply say state machine dot refresh. So if we run this one more time, then we should see, we get Mario, cool. And he's running around. If we click him and click state machine up here, we can turn off looping. So if we turn off looping, you'll notice he stops at the last frame. That's because he'll run through the animation once, then stop. And then if we turn it back on, he'll continue through frames. If we change one of these variables, it changes that individual frames time and everything. And this all just sort of works. So you can actually sort of start building a level, right? If we do this, then we've got a lot of different objects in the scene. And then if we go ahead and add Mario back over here, well, that's not working. So what's going on there? Well, if we press play, then stop, it works, but it's not finishing. And that's because if we go into mouse controls, we basically just need to make sure that we refresh it as we're placing objects here. So we'll just say if new object dot get component state machine dot class does not equal null, then we'll say new object dot get component state machine dot class dot refresh. Okay, so that way as we place it in the scene, it should get the textures refreshed and everything. So we can sort of start building a level now, and it's already turning into something cool. We don't have a question block in here, but I have the sprites and everything there. What I would suggest you do if you want to add the question block, go into our prefabs class, create another function like this. I'm actually going to copy this. Maybe we will do it real quick. So if we just go into here, we'll say generate question block. This will take in the item sprite sheet, and we'll just call this question or flicker animation. This is like the flicker animation, right? And this one is actually going to take 0, 1, 2. And I'm going to change this frame time to 0.57f. We also want this to loop. And yeah, that should be fine. We can change this to like items just so that it's technically correct. The variable names don't really matter. It's still going to work the same. And then we can change this to question block, since that is what this is, just that if we're rereading code later, we won't get confused. Okay, so that should do the question block. And then if we go back into level editor scene initializer, we can go down here, add another button to our ImGui window. Actually, we should copy all of this because we will need to change a few things. So we'll say items equals all this stuff, and then items.png. And then we'll say sprite, remove that so that we don't declare it twice. We can leave all that stuff the same. And then just remove that so we don't set that twice. Remove that so we don't set that twice. And I think that should be good. So now we should be able to add question blocks too. So if we run this again, we got Mario. That's the wrong image. So, oh, we're still using the player sprite. So if we just change this to items, there we go. And then if we change this to generate question block instead of Mario, we should be good. So if we go ahead and redo this and then hit prefabs, we get question block in here. And now we have a flickering question block. So we can add question blocks, Mario, they're all animated. It all worked great. One last thing I will mention very quickly. Notice this little glitch here. We see the gizmos. That is what that is. That's the gizmos, and we don't want them showing up when we're not playing. So just go into Gizmo real quick. Gizmos, or Gizmo system. Maybe not Gizmo system, but if we go into Gizmo itself right here, then in the update method, we can say if x-axis object, or actually let's just make this simple. We'll say x-axis object.get component sprite render dot class dot set color dot set color to new vector 4f 0, 0, 0, 0. Copy that, duplicate it for the y-axis object. Copy both those lines. Actually, I don't think we have to copy those lines. I think that should be it. And then if we click on objects, they still show up. If we click off the objects, but then if we hit play, you don't get that weird
glitch over there anymore. Okay, so that is it for this tutorial. I hope you guys enjoyed it. I hope you guys learned something. We now have animations inside of our game engine. Next episode, we'll go over adding sound, and then hopefully we'll start coding Mario and get the rest of this complete. So I look forward to doing those, and I'll see you guys there. Thanks. In this episode, we will be implementing sound. So you can see here that I have a bunch of buttons, which are all the different sounds I've added to the game, and you can click them to start or stop a sound, and you can play several different sounds, and they are playing through the engine. So this is a pretty big step in our engine because now we will be able to create a full game. We have physics, we have animation, and we have sound. So after this episode, we will actually start building the Mario game, and we will see how we can build a game using what we have so far. Before we start coding the sound, let's just talk about it visually real quickly because there are a few points that I would like to consider before we just jump into coding. Before we start talking about sound, I'd just like to preface this with I am not an expert in sound, and I've done very minimal things with this OpenGL library that we'll be using. So we're just going to be using it for the bare minimum to play a sound. We're not going to worry about velocity, position, anything like that. Even though we do have those capabilities, we're not going to focus on that. Okay, so now what are we going to do to create sound? Well, we're going to be use something called STB Vorbis, which is an STB library for loading Vorbis audio, otherwise known as .ogg extensions, right? You may have seen that. And this is Sean Barrett, right? He's the same guy that we're using to load PNG, JPEG images, and he has developed some really great libraries. This is another one that we will be using. Then we'll be using OpenGL to handle our sound management, to play the sound, stop the sounds, and do all that fancy stuff for us. And the way I want you to think about OpenGL is OpenGL uses something called sources, which are very similar to OpenGL and the thing that we know as textures. Okay, so just keep this in mind while we're developing. OpenGL sources is basically the same as OpenGL textures, and we're even using STB Vorbis, which is very similar to STB image. Okay, so keep these correlations in mind because it will help a lot in your understanding of this. If you understand textures, this should be breeze. Okay, it should be very simple. Now, before we start working with sound, what do we need to know? Well, with sound, you have either mono or you have stereo or you have something higher than that, right? We're not going to talk about the higher levels of sound quality, but I want you to think of this like with images, we have RGB and we have RGBA, right? This is a 3-channel image. This is a 4-channel image. Well, this is a 1-channel audio source. This is a 2-channel audio source. Basically, this means that if you were wearing headphones, this would come out of one side of the headphones. This would come out of both headphones. Okay, most audio that you listen to is stereo. I don't really see a lot of mono around anymore. This is useful if you're trying to do like specific things with your audio, I guess, play certain sounds out of one and the other. But if you're going down that route, you usually use a higher quality audio source. We're using like 4 or 5 speakers, and we're definitely not going to go into that. Okay, so basically we have 1-channel or 2-channel audio sources, mono or stereo, and we're going to be sticking with 16-bit audio sources as our format for OpenGL. Now, how does audio actually work? Well, I'll give you a brief overview of how we'll be using it. So when we call STB, what it's going to return to us is this raw binary data in the form of an array. And this will just be our raw audio data, right? And this is just sort of, we could play through this if we knew how to interface with the lower level system functionalities, right? The operating system. And we said, hey, we've got this data, just play through it. But we're not concerned with that. Instead, we're going to use OpenGL to do that. So we sort of have to buffer this to OpenGL. And then OpenGL will manage this buffer. I believe it's on the CPU side. It's definitely not on the GPU. It could be. I don't think it is, though. I think this is all CPU based, but it will be very similar to how we use the GPU with OpenGL textures. And so OpenGL has this audio buffer, which is very large, and this is like our sound, right? So this is just one individual sound, the same way we would have one individual texture stored on the GPU. Except what OpenGL probably is doing under the hood is using something called a ring buffer. A ring buffer is just a small array, okay? And you have a certain amount of elements in it, and it doesn't go past that. This is a very large array, and it's kind of costly to be carrying this around with you. So OpenGL is probably doing some sort of synthesizing and everything to get all the audio into this one array. And then it tells the operating system, hey, this is the array I want you to play out of. This is where we are right now. And this is where we are in the audio source. So we're at the beginning of both. Then what happens is we just start copying everything from the audio source into here. And then once we hit the end of this audio source, since we're copying, at the same time we're going to be playing. So then by the time we hit the end of the audio source, the audio might be right here, right? We're no longer here because we're playing. So then what happens is if we're here in this array, then we just start copying this data back over to here. And then once we get to here in the audio, the ring buffer, we just loop around and we continue playing. I'm not confident this is how it works, but I'm guessing this is probably how it works because that's how most sound implementations do work. We don't have to worry about any of that though. All we have to worry about is pressing play, stop with OpenGL. That's how simple it will be for us. We do have to worry about one other thing though, which is the concept of a cursor, right? So this is sort of our cursor, and we want to say, hey, we want you to start here, which is 0. That way we start from the beginning of the file. And then if we play, then this cursor will start moving. And then if we hit stop, we might be right here. Then if you want to replay the sound, then you would have to say, hey, set the cursor back to 0. And then just play through again. The last thing I will mention is, if you remember, we had something called GL texture parameter I or something along those lines. And this was our GL way of saying what things we want our textures to do, right? Min mag filters. So like, what do we want to be blurry or pixelated? And we would just sort of set those data and we could do multiple parameters. Well, OpenGL has something similar called AL source I, okay? And this is why, like, keep in mind textures and sound sources. They are very similar the way OpenGL uses it. And that is for a reason, so that it's easy for you to understand. So we can basically set different sound source parameters like the volume. We can set whether it loops. We can set other things among that. Okay, so basically different sound options are what you can place here. If we were doing velocity and stuff, I believe that goes through here too. Not completely sure on that though. Anyways, this is the basics of how this will work. Let's go ahead and start coding and see how this actually works. Very quickly before we start coding the sound, I do want to mention, I noticed a bug while I was experimenting with some things. And if we go into ImGui layer, we should be doing the same thing we're doing for the mouse listener as we do for the mouse scroll back, right? We should say if io.getWon'tCaptureMouse and all this stuff, just to make sure that we're not scrolling if we're in one of the ImGui windows, right? So I just copied this from the mouse capture and ImGui layer down to the scroll so that we're only scrolling if we're in the game view window. We're only sending that to the game. So that's kind of simple, but just want to get that out of the way. Now, the first thing we'll want to do is go to our window class. And this is something that I did forget to mention inside the drawing, but it's not a big deal. To play a sound, you need an audio player, right? So you need some sort of source to play your sound through, which is the speakers. So we need to get a handle to that. And in order to do that, we'll just sort of create a couple of long variables here. We'll call this our audio context, and we'll have our long audio device, okay? And these are two things that are just used by OpenGL, and they make it very simple to use. So we'll go down to our initialization stuff, and right after we make the window visible, we'll set up our audio context. So we'll just initialize the audio device here. And I guess you could do this anywhere. It doesn't really matter. Just make sure you do it before GL create capabilities, because that's probably a good place to do it. And we'll just say string default device name. So whatever default output device they have set, that's the one we will use, is ALC get string. And we'll say device handle 0. We'll use ALC default device specifier, and that should get us the default device. So then we'll just say import static constant, and we will also import this static method. Okay, so that just tells OpenGL to get us the default device name. Then we'll say audio device equals ALC open device, and we'll do default device name. All right, so now we have a handle to our audio device, and now we just want to set up our audio context. So we'll say int attributes equals 0, audio context equals ALC create context, audio device, and attributes. So I think you can set up different attributes. It's been a while, and I don't remember exactly where I followed this tutorial to get all this information from. I'm guessing it was just from OpenGL's website, but basically you can set up different attributes for your audio device. And so we're just saying, hey, our context is using this audio device with these attributes. And we're saying we're not using any attributes and just setting that to empty. Then we'll just say ALC make context current, and then we'll use our audio context. Then we want to say ALC capabilities equals ALC dot create capabilities. So just like we created our OpenGL capabilities, except we need to pass in the device that we're using. And then we'll say AL capabilities equals AL dot create capabilities. Okay, and then that's where we pass in the ALC capability. So I believe this is just like the device, and then this is OpenAL, and we want to change that to AL, not ALC. And then we'll just import that and change that to AL as well, and we'll import that, and we should be good. Cool. Then we just want to say if not AL capabilities dot OpenAL10. So if we don't have the audio library, it's not supported, then we'll just say assert false, audio library not supported. Which you may want to check and see like what the minimum version they support is and everything, just so that you know what your minimum specs are. I'm not completely sure, but I think they go back pretty far, so you should be fine with OpenAL10. Okay, then let's go up to the run method, because after we finish running our game, we just want to make sure that we destroy the audio context. So we will just say ALC destroy audio context, or destroy context, audio context, and then ALC close device, audio device. So we destroy the context and close the device, and we've basically released all that management. If you forgot to do this, it's fine, because the program's exiting right now anyways, and so the operating system would automatically free all that memory and release all the devices that you grabbed a hold of. So it's not too big of a deal, but it's good practice. Okay, so now we want to create a sound, right? How do we do that? Well, let's go to not components. I'm going to put this in Jade because this isn't actually a component that we will be using. It's an asset, right? Just like a texture isn't a component, it's an asset. So is a sound. So we'll go into Jade and create this sound. And I guess you could create a whole audio package and stuff, but I'm not going to go that far. We'll just say private int buffer ID. So just like a texture has texture ID and all that stuff, we're going to have a buffer ID and a source ID. Okay. And then we will have a private string file path, which is just the path to this documents file. Then we'll have a Boolean is playing, and we'll initialize that to false. And we'll have a public sound string file path, so the file we're taking it from, and whether it loops or not. And this is all we will need. So right here we'll say this.filepath equals file path. And then we're gonna use STB to load the audio file, okay? So the way we do this is first we have to allocate some space so that STB can give us information like how many channels we have and stuff. So we're gonna allocate space to store the return information from STB. So we'll say stack push, which basically will manage our memory force automatically so we don't have to free anything. And then we'll say int buffer channels buffer equals stack malloc int 1. So we allocate size for one integer. And whoops, we don't want to create that. We want to import that. So we allocate size for one integer, and this stack push basically ensures that when we pop, this will be freed, so we won't have any memory leaks. Then we'll push one more thing onto the stack because we also want to have a sample rate buffer. So we'll use that, and we'll say stack malloc int size of 1, and this should be lowercase u. Then we're going to use STB to load our stuff, right? So we'll say short buffer, so buffer of shorts, raw audio buffer equals STB vorbis decode file name, and we're going to give it the file path, and we're going to give it the channels buffer, and we're going to give it the sample rate buffer. And I believe that should be it. Let's see if this works out. We'll import this, and that is all we have to pass in. I'll go ahead and just move this to a new line so that you guys can see this whole thing. You gotta love STB and OpenAL and all that stuff, because this is pretty complex stuff that we're doing here, and we can do it in just one function call. It's really nice. Okay, anyways, we'll check and see if we succeeded. So we'll say if it's null, we didn't succeed, then we'll just say system.out.println could not load sound plus file path plus quotation. And then we'll just say stack pop to free up that memory that we used up, and then we'll return import that, and we should be good. Otherwise, if we did succeed, then we want to retrieve the extra information that was stored in the buffers. We can do that very simply by saying int channels. So this is the number of channels, mono or stereo, is just channels buffer. .get. We have one integer in there. We just need to get the first integer and the sample rate. So this will tell us, you know, how many samples we have, and we can just do .get there. Then we'll free that memory. So we'll say stack pop. Then we're gonna wait. Oh, and this should be sample rate buffer.get, not channel buffer or channels.get. Then we just want to find the correct OpenGL format, right? This is just, are we using mono or stereo? So we'll say format equals -1. If we have one channel, then our format is AL format open or mono 16. So we're just going to use mono 16-bit, and we'll just import that. Then we'll say else if channels equals 2, then we have stereo. We'll say format equals AL format stereo 16. Next, we're going to create some space to hold our audio sample with OpenGL. So we'll say buffer ID equals AL gen buffers. This should be very similar, right? This is basically like OpenGL. And then we'll just say import that. Then we want to buffer the data. So we'll say buffer data, doesn't matter. Okay. And I'm using GL here. This is AL. It's so similar that it's starting to confuse me too. Okay. So we'll say AL buffer data. And then what we need pass it is the buffer ID. Then it says format, right? This should all be very familiar to us, which we just got. Then it says the byte buffer. Well, that's our raw audio buffer, which is a short buffer. That's perfectly fine. And then the frequency, that's a little bit different, but that's just our sample rate, which we got from STB. Then we want to generate the source. This would be like generating the texture, right? We just buffered the texture data, really sound data. Now we want to generate the texture, which is our sound or our source. So we'll say source ID equals AL gen sources, right? So we generate one source. Then we're going to set our source parameters or like our texture parameters, right? So say AL source I. Source ID, AL buffer, buffer ID. So that's, we're saying, hey, we're using this buffer for these parameters. Then we'll say AL source I, source ID, and we'll say AL looping is, did they say they wanted looping? We'll do a 1, otherwise we'll do a 0. 1 is true, 0 is false. So whatever you pass in, we just sort of set it. And we'll say AL source I, source ID, AL position, so where's the cursor at? We're going to set that to 0 for now. AL source F, source ID, what is the gain? And I'm going to put this to 0.3F. This is sort of like the volume, right? And one thing I'm going to note too is with textures, we said all this stuff at the beginning. I don't believe you can change it because then you have to generate the texture. With these, you can set this anytime. You don't have to like reload the sound and everything and repeat this just to get a different gain. You can do this at runtime, and we'll see how that works too in a minute. Okay, anyways, after we finish all this, we want to free the STB raw audio buffer. So we'll just say free raw audio buffer. Okay, and we'll import that from, just hit import static method, and that should work good. I'm not sure which library it's importing it from. Okay, so that should load the sound and everything, and very similar to the way the textures work. We're going to also create a delete method so that you can delete this memory if you're done with it. If you switch scenes or something and you have different sounds, you'll want to delete all the old sounds. So we'll say AL delete buffers, buffer ID. That's all you have to do. And I believe you also have to do AL delete sources, and then we'll do the source ID. Okay, so delete the source, delete the buffer, we should be good. As you can tell, I don't use the delete because I usually only have one scene. So yeah. Then we'll make a public void play method. We'll just say int state equals AL get source I. So this is where we're sort of using it at runtime, right? We want to see if it's playing first of all. So we'll say we want to get what the source state is in. So are you playing? Are you stopped? Whatever. We'll say if state equals AL stopped. So the sound has been stopped. Then we'll set is playing to false, just so that we know it's not playing. Then we'll say AL source I, source ID, AL position, 0. So this is that cursor I was talking about. We're just resetting it to the beginning. And we're doing this at runtime, right? We're not reloading the sound or anything. We're just setting it right here. So that's important to recognize. Then we'll say if it's not playing, then we need to play it. And we'll say AL source play. And we'll pass in the source ID. And then we'll say is playing equals true. So basically what this is going to do is it's just not going to play it. So if you hit play twice, it's not going to start playing the same sound, because what will happen is it'll just sort of do nothing, right? So we're checking to see if it's stopped. If it is stopped, then we'll restart it. But if it's not stopped, then we'll just let it continue playing and we won't really do anything. Stop method is going to be a little bit simpler. So we'll just say public void stop. We'll say if it's playing, we don't need to check anything because we're keeping track of that. And then we'll just say AL source stop, source ID. So we'll just stop the sound, and then we'll say is playing equals false. And then finally, I'm just going to create a getter method, get file path, return this dot file path. And we're going to create an is playing method. So public boolean is playing. This one's going to be a little bit more complicated. We're just going to say state equals AL get source I, like we did just up there. Source ID, AL source state. And then we'll say if state equals AL stopped. So literally the same thing we did up there. Then we'll say is playing equals false. Return is playing. Okay, so we basically just want to make sure that if it is stopped, then we know it's not playing, and we'll make sure to send that to whoever's asking for it. Okay, how do we get these sounds into our engine? Well, these are assets, so let's just go to asset pool, and we'll have a private static map of string to sound here. And we'll call this sounds equals a new hash map. Okay, and we will just import that. We should be good. I'll go to the bottom here, and this should be pretty familiar to you by now how we do this. We'll just say public static sound get sound string sound file. Okay, file equals a new file, sound file. We'll check and see if it exists. If we have it, if sounds.contains key, file.get absolute path, then we'll return sounds.get file.get absolute path. Otherwise, if we don't, then we'll assert false sound file not added, just to let us know, plus sound file plus that, and then we'll return null if we did not have the sound added already. Then we'll create an add sound function, which just says public static sound, so it'll also return a sound, and it'll just return whatever you sent it in case you ever want to use it for whatever reason. And then we'll pass in the file, and we'll say whether or not it loops. And I'm just going to copy this little bit right here. If we have it, we just return it. We don't add it again. Otherwise, we want to create a new sound. So let's say sound equals a new sound. This takes in the file path, which is our sound file. Or actually, we could just use file.get absolute path. And then whether it loops, which is the looping. Then we'll say asset pool.sounds.put file.get absolute path, and we'll give it the sound, okay? And then we'll just return that sound. There we go, not too difficult there. I'm gonna do one more last utility method that we don't have with any of the others, which is return a collection of sound, get all sounds. And this will just return this dot sounds dot values. And we'll go ahead and just import that. And I guess we can't use this because this is a static context. That way we can just get all the sounds when we're using ImGui to iterate through all of them pretty easily. So inside of the level editor scene initializer, we'll go down here and we just want to add in another tab. So right here, I'll say if ImGui.begin tab item and just call this our sounds. Then we'll just say collection of sound. Our sounds equals asset pool. Get all sounds, and we'll just import collection here. That should be good. Then we'll say for sound in sounds file temp equals new file. This is just that we can get the file name instead of doing the whole file path, which is a little bit cumbersome. And then we'll just say if ImGui.button, we're gonna do this very simply, temp.getName. So if they click on the button, we'll say if the sound is not playing, then sound.play. otherwise sound.stop. That way, if you click it and it's playing, then it'll stop. And if you want it to play, then it'll play. And then we'll just go down here. We'll say if ImGui.get content region available X is greater than 100. So I just sort of eyeballed that and said 100 should probably be good. We'll do ImGui.same line. So we'll just sort of put the buttons on the same line until we have no more room left, and then we'll move to the next line. Okay, now if we hit play, we should get our sounds, which we do. And we're gonna get an error because I forgot to say ImGui.end tab item. Imported. Okay, if we go back there now and hit sounds, we get no sounds because we didn't add anything. So I'm not going to put you through the agony of watching me add all these sounds. Instead, I'm just going to copy and paste them. So let's go up to our load resources. And right after we load all the images, I'm just going to load all these sounds, which you can find at the GitHub link in the description. And this is just all the sounds we'll be using. So if I rerun that and we hit sounds, then you can see we get all these sounds. And if we hit play, then we start getting the sounds played. All right, so now we have sounds added to our game. We'll actually start building Mario in the next episode since we have all the basics here. So we'll start implementing a player controller and everything so that when we hit play, we can actually start moving around and the animations play at the right time and everything. Yeah, so the game engine is in a good place and we're almost finished with the series. As you can see here, I have done quite a bit off camera. So towards the next few episodes, we will be working towards this, where we basically have a fully functioning, almost fully functioning game. You can see that I have sounds playing and everything, and that the game is kind of working. There are certain features I haven't implemented, and there are still a few different bugs and stuff that I just haven't gotten around to fixing yet. But for the most part, we have a pretty functional game. We will also be adding a lot of improvements to the editor, so we can multi-select objects, duplicate them. So you can see I just duplicated all these, and then you can delete the duplicated objects. You can move them around like I was with the keys and everything. You can move objects using page up and page down, change the z-index order of them. So you can see that I just moved that piece of foliage in front of Mario and stuff. All these different things we will be doing. So it's going to take quite a bit. If you want to take a look at the code that is required to get all this implemented, because I will not be able to get all this code in one episode, then you can take a look at this diff, which is all the different changes. I'll have this linked in the description, but I'm basically going to be referencing this for certain parts that we will be working on throughout today and the next few episodes we will be doing. Okay, so in this episode specifically, we are going to be working on the key combos to do like multi-select type of stuff and draw this box and everything and get the keyboard combos and everything just working really nice with not any major bugs, or at least none that I can find. So let's get back into our code. And just to refresh ourselves, I believe we left off with just implementing sounds, right? So we have our sounds down here, which we can sort of use within the game, which is good. So we can't really do any of that multi-select stuff that I was doing in the editor. And the best thing we can do is, first of all, let's go into our Gizmo class. And inside the Gizmo class, I have this to-do that's been here for a while, which says move this into its own key editor binding component class, which is what we're going to do. So we will grab this, and then we'll go ahead and create a new sort of class over here. I believe inside of components, we have mouse controls. So we'll also add in a new class, and we'll call this key controls. Okay. And what we're going to do is have this extend component. And then if we go back into that Gizmo, we're going to copy this, and we will just move this over to the key controls, right? And we want to put it in its own update method. So we'll say public void update float dt, and we'll just wrap this in that function. And we just need to make sure that we mark this as override. Then I'll go ahead and import the GLFW constants. And now we have a little bit of a problem, right? Because we have the properties window in the active game object. And let me just say too, the code that I've done for this is not code that I would recommend using, okay? I just want to finish the game engine series. So all the code that we're going to be writing is not necessarily the best way to do it, but it gets the job done, which is what I'm trying to do. So with that in mind, let's go ahead and figure out how to get the properties window and active game object into here so that we can actually get these. So the way that I went about doing this is just the simplest way I could think of. Inside of this update method, we're just going to go up here and we'll say properties window equals window.get ImGui layer .get properties window. And I believe we added this get ImGui layer utility function a while ago. So that'll be helpful for that. And then we're going to go ahead and say game object active game object equals properties window .get active game object, which it auto completed for me. So we'll just remove this reference here, and we will remove it here as well. And we're going to change this to properties window .set inactive. And we're actually going to change this up a little bit too in just a second. Let's also move these return statements because they aren't needed anymore since we've abstracted this away into its own sort of class. Before I forget to, let's go into the level editor scene initializer. And we're going to have to add this key controls to our level editor stuff, right? So right below mouse controls will say level editor stuff to add component, new key controls. That way we do not lose the functionality that we already have. And if we go back into key controls, now we sort of want to make sure that this all works right. So right here, this is our duplicate method. One other thing that we want to do real quick is just make sure that the active game object is not null, which it will be able to be when we make some changes inside the properties window too. So that way we just don't try to duplicate something if we don't actually have an active game object. And I'm going to change this to, instead of 0.1, 0.1, we're just going to change this to grid our settings.grid width and settings.grid height. That, or actually I'm just going to change the Y value to 0. That way it just moves over one grid square to the right or to the left, whichever way we want it to go. One of the other things I'm going to do too is we will build this method in just a second, but we're going to want this concept of active game objects, right? Because if we have a multi-select, then there's the potential to have multiple game objects. And so we'll also have a get active game objects function inside the properties window. And this will basically just be like if they have multi-selected and have several game objects selected, right? Pretty straightforward. And so we basically just want to add in support there too. So like if they're pressing the duplicate button, so we'll say if key listener .is key pressed, GLFW left or key left control, and key listener dot key begin press, GLFW key D, and active game objects dot size is greater than 1. So what this basically says is the same exact thing that we have here. If they're pressing the duplicate, Control D, and we have more than one active game object. This will be null if we have more than one active game object. So then that means that if we have several, then it will fall through to this switch statement or this else if statement. And then what we can do is we can say that list of game object or game objects equals new array list active game objects, which will just create a shallow copy of the active game objects. And then we're going to say properties window.clear selected, which is another function we'll add in, which will just clear all the selected game objects. And then we'll go ahead and say for game object, go in game objects. We want to make sure we copy it. So we'll say copy equals go.copy. And we want to make sure we say window.getScene.add game object to scene, and we'll add that copy to the scene. And then we'll make sure to say properties window.add active game object, which is another method we'll add, and we'll just add the copy. So that way we'll basically duplicate the objects and then set all the selected objects to the new duplicated objects, right? So we'll clear it and then we will add those all in. And the delete method, let's just change this up because basically get active game objects will always return all the active game objects. So we only really care about one case here. We'll just say if they press delete, then we'll say for game object go in active game objects, go.destroy. So we'll make sure to delete it. And then we'll just say properties window.clear selected, which should clear all the selected game objects once again. Makes it a little bit simpler for the delete. Okay, so let's go ahead and go into the properties window and we'll add these utility methods that we now need. So we'll go into here and we're gonna have the concept of an active game object, or we're gonna have a private list of game objects, which is the active game objects, right? If they've selected multiple game objects. And we'll just initialize that to null. And then instead of doing this in our ImGui function, what we're gonna do is we're gonna say active game objects.size equals 1 and active game objects.get0 does not equal null. This will just basically make sure that we have multiple game objects selected, or actually that we just have one, right? Because we don't want to show the properties window unless we only have one selected. And then what we'll do here is we'll just say active game objects equals this dot get 0. So it should have the same functionality, except now we have support for multiple. And if we have multiple, we're not going to show the properties window since that doesn't really make much sense. And then let's go down and we're going to fix up a couple of these. So for get active game object, instead of just returning this dot active game object, what we'll do is we'll say, do we have just one active game object? If we do, then we'll return this dot active game objects dot get 0. Otherwise, we will return null. So this way, if we have multiple game objects, we don't end up returning the first object because that doesn't really make sense, right? And then we're going to go ahead and add in our utility function, just public list of game object, get active game objects, and then we'll just return this dot active game objects. And then I'm going to go ahead and expand these. I don't know why IntelliJ does this for me. Don't really like it that much. But we're going to go down here and we're going to say, instead of what we have, we're going to say public void clear selected. And also, we're not using this, so just remove that function. It doesn't really matter. And then we're just going to go ahead and say this dot active game objects dot clear, and that should do it. And then for set active game object, instead of doing this, what we're going to say is if go does not equal null, so they pass in a valid game object, we're going to say clear selected, then this dot active game objects dot add go. That way we make sure that we don't have multiple game objects, and this will just set it so we just have the one, which is what they sent to us. And then we'll go say ahead and say public void add active game object, and this will take in a game object, go, and we'll just say this dot active game objects dot add go. Okay, cool. So that should sort of do it for us. If we run this, we should hopefully have the same functionality, except we're getting an error real quick, which I believe is just because we never actually set active game objects. So we'll say this dot active game objects equals new array list. Yep, not really sure why we're setting it to null up here. We can just sort of get rid of that. And then if we run this, we should get feature parity. So we should have the same stuff that we had before. It should work all the same. So if I click here, not working. So we'll go ahead and see what's wrong with that. And I can see it already. It's probably just this right here. So instead of saying active game object equals picked object, we'll just say set active object to the picked object. And then we can go ahead and try this again. Let's see if that fixes it. Yep, so now we click on it and we should be able to duplicate. And if all went well, I think that should have duplicated it. Not completely sure. I don't think I have key controls. Yeah, I don't think I have key controls. So let's go ahead and check that. We have key controls here. Oh, and I see what the problem is. Inside of key controls, we need to be in editor update, not update. So if we go back into there, we should be able to duplicate. It duplicates and we can delete, and that should delete. If I delete that, it'll be a little bit more clear. There we go. So that's all working properly. Good thing we have that fixed. Now let's try and add in the multi-select box, right? First of all, in order to add that in, we're going to have to update our picking texture, which it won't be that hard actually. So right now in our picking texture, we just have this read pixel function, and we will actually want a read pixels function, right? So we'll take in an int x, int y, and then an int width and an int height. This way we can read a block of pixels from the screen and basically just go through each one of those and check and see what the IDs are and return it to whoever asked for it. And we're going to actually return a float array to the caller. And I'm actually going to simplify this a little bit more. Instead of doing this, we're going to say vector2i start, vector2i end, which is just a vector2 of integers. Okay, and that should be good. Then what we're going to do down here is we're going to say vector2i size equals new vector2i end dot sub start. So we get the size, which is the block of pixels, how big it is. And let's also make sure we take the absolute of that. That way, if they like click and select to the left or to up to the right, and no matter what direction they click and drag, it will always give us the positive size. And then we can get rid of, or actually we're going to change pixels to, instead of 3, we're going to say 3 times number of pixels. And how many pixels do we need? Well, we just need the area of the square that we selected, right? So float number pixels, or actually that should be an int number pixels equals size.x times size.y, which is the area of the square, right? So that should give us enough pixels. And then we can just say, instead of GL read pixels like this, we'll say start.x and start.y. And instead of width 1, height 1, we'll say size.x and size.y. And that should give us everything we need. Then we will simply return the pixels. But we do need to do one more thing. Since we are storing all of our IDs plus 1, we want to make sure to subtract 1. So we'll say for int I equals 0 until I is less than pixels.length, I plus plus, and then we'll say pixels I minus minus, or minus equals 1. So we'll just subtract 1 from each one of those. That way we get the appropriate game object IDs from these pixels. Okay, one other thing we're gonna have to do is let's go to the mouse listener, because I did put some changes in here too, just to make sure that the dragging and everything is working correctly. So inside of the mouse listener, right up here, I added in just a couple of functions that will help us out. Public static void end frame, which I know we just removed in like a couple episodes ago, but we're adding it back now. And then we're gonna have public static void clear. Clear, we're basically just gonna reset all of our values. So we'll say get.scroll x equals 0, get.scroll y equals 0. And I think we can actually probably just copy all of this stuff and then we'll paste it here. And then we'll just replace all of this with get, because we're basically doing that. And then we're gonna say get.mouse button down equals 0, get.isDragging equals false. And then we'll say arrays.fill get.mouse button pressed with false, which will basically just fill the array with the value false. So we'll reset all the mouse buttons so that nothing is there. So this clear function is just something that we will use at certain times. We'll see in just a minute. And then right here in end frame, we're just gonna say get.scrollY equals 0 and get.scrollX equals 0, because I was having some trouble where this was not getting called all the time, and that was not good. So inside of our mouse pose callback, what we're going to do is, instead of doing this reset dragging, basically, if the mouse button down is greater than 0, we're going to change this up to say if not window.get ImGui layer .get game view window, which we're gonna add. And this is one of the parts where, like, I don't like how this works, but I'm just doing it because it will get our job done very quickly. And we're gonna say get want capture mouse. So if the game view window doesn't want to capture the mouse right now, we're just gonna clear all the values, because basically we don't want our key controls to be doing anything if we're not hovering within the game viewport. Okay, so let's go to get ImGui layer, and then we'll go into the ImGui layer, and inside of here we will just add in a method that says public game view window, get game view window, return this dot game view window. Okay, and then we can go back into the mouse listener. This should be good now, and we should be all good there. And we're gonna add a couple more utility functions in here. So right above get screen X, I'm gonna add in public static vector to F screen to world, which should convert screen coordinates to world coordinates, and we'll take fin vector to F screen chords. And we're also going to have public static vector to F world to screen, which will take in a vector to F world coordinates, just so that we can go back and forth, right? Because these are two very useful functions, and we're going to need them coming up. So we'll say vector to F to go from screen to world. We're going to say the normalized screen chords equals a new vector to F. And we're going to take whatever screen coordinates they passed in. So we'll say .x over window.get width. And we'll say screen chords.y, whatever they passed in, over window.get height. So what this is going to do is it's going to change our screen coordinates from 0 to window width on the x and 0 to window height to 0 to 1 on both of these, right? So we're normalizing them. Then what we want to do is we want to multiply that by 2. And we want to make sure we subtract 1 from both of those. And what this is going to do is shift it so that now our coordinates are on a range -1 to 1, right? So basically we've gone to screen coordinates now to normalized device coordinates, which is sort of the same thing OpenGL does, and what we're doing in our shaders, right? Because that is how you go from screen to world coordinates. Then we'll say camera equals window.getScene.getCamera. Or I think .camera. There we go. And we're going to create a temporary vector for F, which is going to have our normalized device coordinates. Or I guess it's called normalized screen chords, but at this point they are normalized device coordinates. And we'll say use X, Y, and then we'll just do 0, 1 for the Z and W. I will move that down to a new line so you guys can see that. And make sure that this is an equal sign. So we have this temporary vector X, Y, and then 0, 1. We've just sort of moved this into vector 4. Make sure to keep W to 1 too, because if you don't, you will get problems. And then we'll have matrix 4F inverse view, which equals a new matrix 4F camera.get inverse view. And then we're going to have a matrix 4F inverse projection, which is the camera's inverse projection, right? We're basically going backwards, and this is how we do it. We use the inverse. Then we'll say temp.multiply inverse view.multiply, and make sure you do parentheses exactly the same here because this is important. And we're going to do inverse projection. This will just undo all of the things we did to get it to screen coordinates. Now we're basically going backwards, and we should have it back in world coordinates. So we've undid everything, and then we can return a new vector 2F temp.x temp.y. Okay, so the math here is fairly straightforward. If it confuses you, I suggest taking a look at some abstract algebra books, or I'm sorry, not abstract, but linear algebra books, and possibly looking at a few different answers on why this works the way it works. In OpenGL, we basically do projection times view times model, right? That's what we do there, and that gives us our screen coordinates. So if we want to go to world coordinates, which is basically the reverse of this, what we do is we would just do inverse projection. So that would be like this. It's not really raising it to a power, it's just the inverse, times the inverse view, times the inverse projection, right? And I actually did this a little bit wrong. We just want the model, right? Or I guess this would be the screen coordinates in this case, right? So we take the screen coordinates times inverse view times inverse projection, which is what we're doing here. And that gives us world coordinates. So we're just reversing this. That's all we are doing. Nothing too complicated. And then here, we're just doing it in the correct order. So it's going to be very similar. We'll say camera equals window.getScene.camera. And then we're going to say vector 4F NDC space pose. So the normalized device coordinate space is a new vector 4F world coordinates.x, world coordinates.y. And then we're going to say matrix 4F view equals a new matrix 4F camera.get view matrix. And then we're going to say matrix 4F projection equals a new matrix 4F camera.get projection. And let's also add in 0, 1 here. Once again, don't forget the 1, that is important. And then we're going to say NDC space pose.multiply projection.multiply view. And order of parentheses and everything matters a lot here as well. So now we're just going the correct direction, right, to get us into basically screen coordinates. So then we're going to say vector 2F window space equals new vector 2F NDC space pose.x, which it really isn't anymore. And then that dot y, and we're going to multiply by 1 over NDC space pose dot w. So basically this multiplying by the w is sort of like, this is almost like the FOV or something. I can't really remember off the top of my head exactly why the w works, but we basically want to make sure that we multiply by the inverse here, because when we're doing all the matrix multiplication up here, that w ends up becoming very important. And this basically undoes what we do through this matrix multiplication. Okay, then we're going to say window space dot add new vector 2F 1.0F 1.0F dot multiply 0.5F. Look, it's the reverse of this, right? We did multiply by 2, subtract 1. Now we're adding 1, and we're multiplying by a half. So same exact thing, we're just doing it in reverse. And then we'll say window space dot multiply window our new vector 2F window.get width window.get height. Okay, and if we take a look at multiply, because I wasn't sure if this would do the correct thing, but it does. This just is component-wise multiplication, which you can see right here, and it basically just x times x, y times y, which is what we want in this case. Okay, so then we can just say return window space. And that should get our world to screen. So now we have screen to world coordinates, world to screen coordinates. Those are good utility functions that we will be using. Let's go into properties window too, because basically what I want to do is, this is mouse control stuff and it shouldn't be hidden in the properties window. So we're going to copy all of this and then we're going to go over to the mouse controls which is really where that belongs. And then we're going to put this inside of our editor update method here. So we'll basically just do this, and we already have a debounce in here, so that's good. We should be mostly good here, except we just want to make sure to grab the picking texture. So we'll say picking texture equals window dot get ImGui layer dot get properties window dot get picking texture. And I think we just deleted that method, but now it's actually important. So let's go to properties window, and we're going to add that back in. So we'll say public picking texture, get picking texture, return this dot picking texture. Okay, and then back into mouse controls. So we're getting that. We should be good. And then we're going to also go ahead up here, and we're going to say scene, current scene equals window dot get scene, because we will be needing that as well. We'll just import that. And that should get us this. So we're almost back to where we were. And then right here, we basically just want to add in window dot get ImGui layer dot get properties window dot set active game object. So that should fix that. And then right here, we can just say window dot get ImGui layer dot get properties dot clear selected. Okay, and that should do the same thing for us, right? And this should basically be feature parity with what we had. So I'm going to go ahead and I'm just going to do one thing to simplify this and move it down to here. We'll say else if, which should just sort of chain our logic together with this. So basically, if they're holding something, then we don't want to take over here, right? Because they're trying to place something right here. And if they're not trying to place something and they click on to the screen, we want to check and see if they clicked an object. And if they did, we'll set it to the selected object. Okay. And let's go back into the properties window, and we'll just remove that code if we didn't already. I'm not sure if we did. Yeah, we left it in here. So we can just remove this whole update method now because it's not really necessary. And we'll go ahead and remove that debounce as well. And let's go ahead, and if we hit Shift F10, we should still be able to do the same thing. We've got an error, which is just we don't have this function anymore, which is fine. We'll just remove it. And if we click, we still get the selected game object. If we click off, we don't. Okay, cool. So that's still good. We have all of that working properly. So we've just sort of abstracted some logic there. Let's go back into the mouse controls, because now we want to add in new mouse controls, which are basically the dragging that I showed you, right? So we'll go down here and we'll say else if the mouse listener is dragging and mouse listener mouse button down, GLFW mouse button left. So we'll basically just check and see if they are dragging and they're pressing the left mouse button. We're going to have this helper variable. We'll say if not box select set. So basically, if they haven't started already, we'll add this up to the top. So basically, this will be a Boolean that tells us that they have started dragging the mouse, right? So we'll say private Boolean box select set equals false by default. So basically, if they have not set it, then we want to mark where they started to click and drag. That way we have that position. So we'll go up here and we'll also have a private vector 2f, which is box select start, and we'll just initialize that to an empty vector 2f. And then we'll also have a private vector 2f box select end, which is also an empty vector 2f. Then we'll scroll back down to here. So if they have not started dragging yet, then we'll say window.get ImGui layer .get properties window .clear selected. So we want to make sure we clear anything that is selected since we've started dragging the mouse. And we'll say box select start equals mouse listener .get screen coordinates. So this will basically just get where the mouse is on the screen. And then we'll say box select set equals true. So we basically say, okay, make sure not to keep resetting this over and over again because we know we're dragging the mouse now. And then what we'll do is we'll just say box select end equals mouse listener .get screen. So every frame we'll just keep setting that over and over until they stop selecting. And then we're gonna say vector 2f box select start world. So the start in world coordinates is mouse listener .screen to world box select start, and vector 2f box select end in the world is equal to mouse listener .screen to world box select end. So now we have the beginning and the end, and then we're just going to do one more helpful thing, which is half size, just so that we can draw the green box. So we'll say is equal to new vector 2f box select end world dot sub box select start world, and I will move this to a new line because that's getting big. Dot multiply by 0.5f. So we basically just get half the size of whatever they're dragging, and then we can say debug draw dot add box 2D, and we'll say new vector 2f box select start world, and we'll want to make sure to add the half size, and then we'll say new vector 2f half size dot multiply by 2.0, and then rotation will set to 0. Okay, so basically we just had to do this a little bit weird because we have the start, but when we add the box here, we want the center, so we added half the size to get the center. Then we multiply the half size by 2 to get the full size, and that should add a green box. So if we go ahead and we click, when we click and start dragging, we should see a green box, but we're not. So I know exactly what's going on there. We basically just want to make sure that we're calling end frame inside of our window. At least I suspect this is what's wrong. So let's go into the window class, and right down here, right before we swap buffers, I'll go ahead and say mouse listener dot end frame, and I think that should fix our problem. So if we go back in, one other thing that I will mention real quickly while we're solving this bug is to go into ImGui layer, and then inside of the scroll callback, just add an else here and then clear the mouse listener. That was for another bug where basically if you started scrolling out, then it would continue scrolling even though you didn't want it to. So this should fix that problem. Now about this bug though, let's see what's causing that. And it looks like I was just dumb and accidentally deleted a piece of code that was important. We should have left that get.mouseButtonDown is greater than 0, get.isDragging is true. Okay, so with that out of the way, now if we click and drag, there we go. You see we get this green box and it's not quite right. Why is it not quite right? The Y is off. Well, I think that's probably has to do with the window. If we go into the window class, you'll see that what I'm returning inside of get width and get height is the actual width and height, which you would think is good. But in a lot of cases, what I'm actually expecting is the frame buffer size, which is always 3840 by 2160. And this is not a float. So instead of this, if we return whatever your actual window size, what the full screen window size you would expect it to be is, if we do that, I think, yeah, now it's corrected. This bug threw me off for such a long time because I had no idea what was going wrong, but there is basically just a big gap in my knowledge and what I was expecting and what I was actually getting. One thing that you'll notice is we never reset it. The start is always the same. So once we actually finish selecting, if we go back into mouse controls, how do we know when they've finished selecting, once they've released the mouse? Well, we know that if they're not dragging, if they're not doing anything, but box select is set, that means that they did drag. And so if it is set, then we basically want to just make sure we set it to false, which will allow us to reset it, right? So if we do that, then we go into here, you'll see that it resets now. But this also tells us once they're done dragging, so we can check and see if they actually multi-selected anything, right? So we'll say int screen start x equals int box select start.x, and then we'll say int screen start y equals int box select start.y, and we'll say int screen end x equals int box select end.x. I'm sure you can guess what I'm going to type next. So we're basically just getting all these values, which we're going to use in just a minute. And we'll say box select start.0 and box select end.0, just to make sure that those values are completely reset. And then we'll say if screen end x is less than screen start x, we just want to swap them. That way we have these in the correct order. So we'll say int temp equals screen start x. And then we'll say screen start x equals screen end x. And then we'll say screen end x equals temp. So that should swap those values. And then we'll say if screen end y is less than screen start y, then we do the same thing. We'll say int temp equals screen start y, screen start y equals screen end y. And then we'll say screen end y equals temp. Okay, and that should swap the values first. So now we have them in the correct order. Screen start is on the left, screen y is on the bottom, as it should be. So we can say float game object IDs, and we'll basically just read all the pixels that are there. So we'll say picking texture.read pixels, and we're going to give it a new vector 2i for the start, screen start x, and screen start y. And then we'll give it a new vector 2i for the end, which is screen end x and screen end y. And that should be good. We should get a set of game objects. So we'll import that. This should be our game object IDs. And then what we're going to do is we only want the unique IDs, right? We don't want to add the same game objects multiple times. We just want the unique set. So we can use a set, which should give us just unique things. So a set of integer unique game object IDs equals a new hash set. So this is just a simple data structure in Java, which should make our lives a lot simpler. And then we'll go ahead and do this as well. And we'll just say for float game or object ID in game object IDs, unique game object IDs dot add int obj ID. And this will just make sure that we get a unique set. So when we add to the set, if we already have one of these IDs in here already, it won't add it twice, which is perfect. That's exactly what we need. Then we'll say for integer game object ID and unique game object IDs. So now we're going to loop through the ones we picked up, and we'll say game object picked object equals window.getScene.get game object by the game object ID. So we'll just pass that. And we'll say if the picked object is not null and the picked object does not have the non-pickable component. So if that is null, which basically means that we can pick it, then we'll just say window.get ImGui layer .add or get properties window .add active game object picked object. Okay. So now we should have multi-select. This should select all the game objects and add it if we don't already have it. So if we go into here, select all of these, and I hit delete, you'll notice that I almost deleted all of them. We didn't get this deleted. Why? Because we had two of them. It's also interesting, if we select just one object, it just adds it as the active game object, right? And it doesn't matter where the box is, it just has to be in the correct bounds. One last thing I'm going to change real quick is if we go into the window, or actually I think the render, we basically just want to make sure that our lines are on top. Actually, let's go back into window. Okay, so you'll notice when we go back into the game, when I drag the green box below these objects, you can't see it because it's not on top. Well, we can change that very easily in the window by just saying, let's do our debug drawing. So we'll copy this and we'll do it after we render the scene. That way it's on top. So if we go back in, now we have this on top, and debug drawings will always be on top, which is nice. So if we go, we select, we multi-select, that works fine. That's good. Okay, this tutorial has gone on for a long time, and I have a feeling the next few tutorials are also going to go on for a very long time too. If you want to check out all the source code that I have showed you at the beginning, you can look at the link in the description. In the next episode, we'll continue working on the mouse controls and stuff and be getting a few more things. Like I just selected these two objects, which if I delete, you can see, or actually I selected more, but it's hard to tell because we have no way of knowing, right? So one of the things that I implemented in the actual version is like highlighting, right? If I select objects, it highlights which objects I selected, so you know exactly what you've clicked on and all that stuff. So we will implement all of that and more. One other thing I also implemented was if we place multiple objects, I still have some debug drawings going on, but basically it will only select one of each object even if you're holding down the mouse button, which you can see by that. We get some weird errors with the line staying on for a little bit too long, but you get the point. In this episode, we will be going over highlighting selected blocks, so that should be very quick and straightforward. We will also be going over adding multiple blocks at the same time, so you can see that as I'm clicking over here, all those objects only get added once, and then you can see once I deselected all those, they turned off. So all those objects were only added once. We will also go over fixing the grid lines. All this should be fairly quick. So you can see that the grid lines work when you zoom out and when you zoom in. And I also added some optimizations so that as you zoom to a certain point, the grid lines just sort of disappear. So we may or may not talk about that today. And then we will be adding in physics callbacks to our components and physics functions. So we'll be adding the ability to raycast into the world and have a callback call some components. So like player controller has callbacks that tell me, hey, I've begun to collide with an object, and it tells me what the object was, what the contact normals are, and all that good stuff. So we will be implementing all of this today.
And yeah, let's get to it. Okay, let's get around to doing that first thing that I talked about, which is highlighting the blocks when you select them. Well, that is actually fairly simple. And I don't know if this is the standard way people do this, but hey, it was the simplest way that I could get this done. So basically, inside of our properties window, which you can see I just switched to, I'm going to add a list that is tracks with our active game object. So the indices will be the same, and honestly, it doesn't really matter too much, but it is kind of important. So it'll just be a list of vector4f, which is going to be our active game object's original or OG color. And basically, this is just going to contain the color they were before we selected them, because we're going to be changing their colors on select. And then we, of course, want to initialize that list just so that we can use it. So one thing we will want to do is scroll all the way down to where we have our clear selected function. Now, actually, I guess it probably makes more sense to do the add active game object function first. So when we add a new active game object to our list, what we want to do is we basically want to get a hold of its sprite render, if it has one. If it doesn't, I guess this will really be too useful, but we'll go ahead and get that. So we just get the sprite render.class. And then we can say if the sprite render is not null, then we just want to say this dot active game objects dot or OG color dot add a new vector for f and copy the sprite's color. So we simply make a copy of its color, and then we can say sprite dot set color, and we will just set it to a new vector for f 0.8f 0.8f 0.8f. So it'll make it like a yellowish color that is semi-transparent. So that should be good. And then we'll say otherwise, since we want this list to basically track with the active game objects exactly, we'll just say this.active game objects OG color dot add new vector 4f. So since there's nothing there, we don't really need to add a copy of the color. We just need to add an empty vector so that we keep these lists indices the same with the objects that they have. Okay, and then once we clear selected, in order to get it to set back to the original colors that they had, we'll say if active game objects .og color .size is greater than 0, and then we'll just loop through. We'll say int I equals 0, and then we'll say for game object go in active game objects, and these sizes should match up. Then we'll just say sprite render SPR equals go.getComponent sprite render .class, and we will simply say if the sprite is not null, then we'll say sprite.setColor active game objects OG color.get I, which should set the color to the original color that it was. And then of course we just need to say I++ so that we keep that index current. And then we can clear the game objects, but we also have to clear the OG color just to make sure we keep that all the same. Now if we go in and we select multiple objects, we're going to get an error. Let's see what's going on. It says we get a null exception, and that is because something is going on. Oh, because I set the wrong list here. We want to set active game objects OG color to a new array list here, not the active game objects, which we've already set. Okay, now if we go ahead and select multiple things, you can see it sets them all to a different color, and if we click off, it resets them. And these ones aren't quite right. Are they a different color? Oh, and you know what? I think these ones look different because this is a block underneath the block, right? So if we delete, we actually had multiple blocks placed there. And that's another thing we will be fixing today. So I'm just going to go ahead and delete everything so that we can sort of have a fresh slate. Okay, play stop that just to save that. Now, if we go back, we basically want to improve it so that when we're placing multiple blocks down, right, when we go and do that, we don't get doubles placed down on accident, which you can see I got a double there because we just placed it over the same area. So we can do that by just going into our mouse controls class, and we'll add in a little bit more of a helpful thing. So first of all, we're going to sort of get rid of the concept of the debounce time for placing blocks, and we're going to change that to 0.2f. And then we're going to go down here and when we're checking, so we say if holding object is not null, I'm going to get rid of this completely because we're going to check something different. What we're going to do is right here when we say if they press the left mouse button, instead of placing, we're going to say float half width equals, and we're going to get half the width of the grid width. And then we're going to say half height equals settings dot half the grid height. And then we're basically going to say if the mouse listener is dragging, so if they're dragging the mouse, which would happen if they're just moving it, right?
And we're going to create this function where we basically check to see if there is already a block in the square that they're trying to place the object in. So we'll say, and there's not a block in the square. We're going to say holding object.transform.position.x minus half width. And you'll remember holding object transform position x is the center of the grid square that we're hovering over right now. And then we'll say holding object.transform.position.y minus half the height, which should give us the appropriate thing. So once we implement this function, not block and square, and I'll move this to a new line, we should basically be checking to see that there's not already a block in the square. Otherwise, we're checking if the mouse listener is dragging here, and we also need a bracket here, and we're just going to surround the place function inside of this bracket, and we're going to remove that debounce equals debounce time because that doesn't really matter. And then we'll say otherwise if the mouse listener is not dragging and debounce is less than 0, so this is where we will use a debounce. We'll say place, and then we'll just say debounce equals debounce time, which should do it so that if they're single clicking, they won't double place on accident. Now, this block and square function is the part we have to now implement real quick. So how does this work? Well, basically what we're going to do is we're going to scroll all the way down, and then we're going to say private boolean block in square, and this will take in a float x, float y. So that's basically the bottom left corner of the square. And we're going to say properties window equals window dot get ImGui layer dot get properties window. Then we're going to say vector 2f start equals new vector 2f xy. Vector 2f end equals new vector 2f start dot add new vector 2f settings dot grid width and settings dot grid height, right? So that should be, the start will be the bottom left corner, end should be the top right corner of the grid square that the mouse is currently hovering in. And then we can say vector 2f start screen f equals, okay, and the reason I'm calling this f is because we're going to be using floating points here, and you'll see in a minute why. So we'll say that's the mouse listener dot world to screen, and we'll give it our start. So we're converting from world coordinates to screen coordinates, and then we want to do the same thing for our end screen. So we say end screen f equals mouse listener dot world to screen end, and then we'll say vector 2i start screen equals, and then we'll say new vector 2i, and we'll cast it. So we'll say int start screen f dot x, and I'm gonna add 2. So this will basically like add 2 pixels to where the mouse is in. That way we're kind of going inside the border of the box a little bit, so we don't pick up any objects in a different grid square. And then we're gonna say int start screen f dot y plus 2, and then we're gonna say vector 2i end screen equals new vector 2i, and to keep it even, I'm gonna go end screen f dot x minus 2 and int end screen f dot y minus 2. So that way we just kind of get a little bit inside the grid border instead of that way we don't accidentally pick up extra objects or something. And then we can just say float game object IDs equals properties window dot get picking texture dot read pixels, and then we'll give it the start screen and the end screen, and that should give us all the game object IDs within this. And we'll do something very similar to what we did above, and we'll just say for int I equals 0 until I is less than game object IDs dot length I plus plus, and we'll just say if game object IDs I is greater than or equal to 0. So if we have a valid game object, we'll say game object picked object equals window dot get scene dot get game object, and we'll say int game object ID is I, so we just have to cast that to an integer. And then we'll just say if the picked object dot get component, so if it doesn't have the non-pickable class, that way we don't accidentally select the object we're holding, then we can just return true. All right, and then we'll return false other way. So we're just looping through all the game objects, and if we find one that's a non-pickable, then we'll say, hey, there is a block in this square already. Otherwise, we just return false. So it's all conceptually kind of simple. We just have a lot of casting and stuff going on here, which kind of bloats the size. But with this in place, we should be able to go into here, and if I click and drag, something's not working because I'm getting a lot of game objects, so it's clearly duplicating. Let's see what's going on. And I know exactly what the problem was. Right here, I'm checking to see if it doesn't have non-pickable. No, we want to check and see if it, yeah, I was checking to see if it did have it. We want to check and see if it doesn't have it. If it doesn't have it, then we return true. And with that change, we should be good. So if we go back into here, you should see over in the scene hierarchy panel, as I add objects,
it only adds one at a time. So this means we are only ever getting one. And then we can also see this, if I go ahead and just select all these and delete, you can see there was only one of each in the squares. So with that out of the way, we now have like a little bit more of an easy to develop editor, right? We can select multiple objects, we can drag without worrying about like accidentally doing too much. We can select multi, duplicate, and we can't really move those yet. And it seems like the duplicate button is not working, so maybe we don't have that enabled yet. Okay, and I have a feeling the duplicate key is not working because of this other change I made. So real quickly, inside of key listener, just go ahead and instead of doing this thing for key begin press, which is kind of stupid because if you press one key and you want to check it in multiple different functions, it's not going to work right. Because if you're checking one function, if the D key is pressed, then you check in another, it'll already be set from the one function. So instead of doing this, we're just going to return get.keyBeginPress key code. And we're not going to do any bounds checking just so that we know if something is wrong. And then we're going to add in one frame in here to help us out. And this is going to be public static void end frame. And we're just going to say arrays.fill get.keyBeginPress false. That way, every frame, we're basically saying, okay, if we began to press a key on this frame, we are no longer going to do that. And then we should be good. So this should only trigger once per frame. And then the next time they press down, it'll trigger again, since we have it on press, setting that to true. Okay, so with that, we should be able to go into our window class real quickly. And then we can just add right by mouse listener.endFrame. We can say key listener.endFrame. And that duplicate function should work properly now. Let's see. So if I go ahead and do that, and then I just duplicate. Okay, yeah, now you can see we've got duplicated objects. If I delete those, you can see we have some extras there. Okay, so with all of that out of the way, let's move on to physics, okay? I'm going to go ahead and show you guys how to implement the different physics callbacks and stuff using Box2D. Now, you guys know me though, and before I go ahead and show you how I implemented these things, how do you find out how to implement callbacks and stuff for Box2D? Well, you go to Box2D's documentation, which is plentiful and helps you a lot. Exactly how I figured this out was I just looked over here and I was like, okay, I want to add callbacks for when two bodies begin colliding. So I looked in bodies, and then you can see, let's see, is there anything in here? No, there's nothing that talks about collisions. Well, what about contacts? Okay, that probably makes more sense. And then contact listener. And then I go into here, and if I click onto contact listener, you can see he says you can receive contact data by implementing this. And so then I implemented it and I started experimenting, and I came up with a solution that I thought was pretty good. And I'll show you what that solution is now. But if you ever want to do this in the future, look to the documentation. It helps a lot. As for how I implemented the contact listener though, let's go into physics, and we're going to go ahead and add a new class. And we'll call this Jade Contact Listener. I'm not using the name Jade anymore because it's actually used by Blizzard. I think they have an engine called Jade. But since this series started with Jade, it's going to be Jade for this series. Okay, so we have our Jade Contact Listener, and this implements Contact Listener, which is an interface that we can import from Box2D. And if you hit Alt-Enter, you can say implement the methods, which will get you all the function definitions. And we basically just want to create something that gives us an easier way, because right now, you can't really easily get this to all of your components, right? What we ultimately want to be able to do is say something like, hey, I have some specific component, maybe it's the sprite render. More likely it'll be a player controller or something, which we will see. And you want to be able to say like override public void begin collision, right? And this will basically give you a game object, and it'll give you other stuff, and then you can start handling collisions, right? That's how simple it will be. So the way we can do that is we can use this as sort of a wrapper and then give us that functionality. This also makes it nice if you ever want to switch physics engines. You don't have to change too much. You just have to keep that functionality the same for the components and sort of forward that functionality to the new engine or the new physics engine. So what we can do is, if you see contact has this thing called user data. Let's see. Well, you can say get fixture. So this is like the collider, and fixture A is collider on object A. And then you can see this has user data. And user data can be whatever you want. If we look at the type, if you control and you hover over this, you can see this is just an object. So we will be setting that object to our game objects, which we can do by going into physics 2D. And we're going to go ahead, and when we go and set certain things, like you can see we've got circle here. We'll do box collider since this one's a little bit more simple. But you can see we have the shape, and we say shape.set as box. And I'm actually going to change the way we do this a little bit more. Instead of doing this body.createFixture, what we're going to do instead is we have our shape. Okay, and we're going to change the way we do this a little bit more. We're going to abstract some things and just make this a little bit simpler. So let's go ahead and we're going to add in a function, and we're just going to call this private void add box2D collider, which will take in a rigid body, RB, box2D collider, box collider. And this is basically just going to be everything we had in here. This way we can abstract this logic away, and we'll add it right here. And let's actually make this public because we may want to use this from external classes. And then what we're going to do is, first of all, we're going to say body equals rb.getRawBody. So we're going to get the raw body from that, the box2D body. And then we're going to say assert body is not null. Raw body must not be null, which we'll make sure is always true. And then we need a shape. So we'll say polygon shape equals a new polygon shape for this specifically. That way we have that shape set up. And we're going to change the way we do this a little bit too. So you can see that we have, we're setting this to the origin, and then we're doing like this offset thing, which is just not the best way to do this. Instead, what we can do is we can say, set this to the offset, and then we can just get rid of this, which is much simpler than what we were doing there. Okay. And then finally, we can say fixture def. So this is like the fixture definition equals a new fixture def. We'll say fixture def dot shape equals the shape. So we assign the shape, then fixture def dot density equals 1. This is important just so that you have a uniform density or whatever. If you wanted to be more physically accurate, you could change this to something and actually make it customizable and stuff. Then we could say fixture def dot friction equals rb dot get friction, which I'll pin that, and we can do that a little bit later when we work on more physics. Then we'll say fixture def dot user data. This is the important part, okay? Is equal to box collider dot game object. So we've assigned this to the fixture's data. Now we will be able to access this, okay? Then we'll say fixture def, another thing that we're gonna pin and do later, is sensor equals rb dot is sensor. And I'm just gonna comment that out for now. We will add that later on. Then we can just say body dot create fixture, fixture def, and that should take care of everything for us. And then up here, I'm just simply gonna say, instead of this, we can say add box collider 2D, and we'll give it the rigid body. And then we can say for the box collider, and we should be good. And I'm gonna change this to an if, because we are gonna want to add multiple colliders to a single game object, and this will just allow us to do that. And then also we're gonna move this up here, and we're gonna get rid of shape. We're gonna get rid of this, and we're going to implement circle collider later on as well. Okay, so just a few different changes, sort of changing the way we do this a little bit. We'll make it nicer in the future when we add in more physics functionality. Anyways, the whole point of this, and one other thing we want to do as well too, is say up here, because we will probably want to get it here too, bodydef.userData is also the rb.game object. So all user data will always be game object, whether it's attached to a collider or whether it's attached to an actual body. It is always going to be the game object, which is good because now we can go into contact listener, and we can say game object, object A equals cast to a game object, contact.getFixtureA.userData. And what this should do is get us that game object that we set. And I'm just going to change that to get user data. It shouldn't make a difference. But anyways, that's just going to get us that user data that we set at the beginning. And then we're going to do the same thing here. Just change this to contact.getFixtureB.getUserData. Same thing. Then what we're going to do is the world manifold, which is sort of the collision information. It gives us the contact normal, which faces we're colliding, all sorts of different things. So world manifold is very useful, and it gives it to us in world coordinates instead of local coordinates, which is nice. So we're going to say world manifold equals new world manifold, and we can get the contact information in world coordinates by just saying get world manifold. And we pass it the manifold. And so this uses the contact, which we were passed, and sort of converts it to world coordinates instead of local. And then we can say vector2f a normal. So this is object A's contact normal, basically the direction the other object is hitting A at, is equal to a new vector2f, world manifold.normal.x, world manifold.normal.y. Okay,
So that is it for A, and then vector 2f B's normal is just going to be the same as vector 2f A normal, except we're going to negate it because B, everything is acting the opposite direction for B. So we just want to make sure to keep that in mind when we think about B's normal. Its local stuff is sort of opposite to what it is to A. Then we can say for component C in object A dot get all components, and we'll go ahead and import this. We will say C.begin collision, which is the function we will add. Object B, so it's colliding with object B. Its contact is the same contact, so we'll just forward this contact information if they want anything extra. And then we'll give it A's normal, so the contact normal according to A. And then we'll just do the same thing for component C in object B dot get all components, C.begin collision, object A, because according to B's components, it's colliding with object A. We'll give it the contact and we'll give it B's normal. So we basically just call these on both objects because for every contact, we will only get called, this pair of objects that are colliding will only be called once. And so we're basically going to go notify each component in each of their respective game objects that they were collided with. Let's go ahead. We want this function definition. I'm going to copy that and then we'll go to component, and I'm just going to add it like right above ImGui right here. Okay, so let's say public void begin collision. Actually, we copied that for a reason. This is a game object. This is a contact, and this is a vector 2f. Okay, and we're going to go ahead and import this from Box2D. And if you wanted to make this completely agnostic to the physics engine, abstract the contact. That way you're not depending on Box2D explicitly like we are here. I don't care too much because Box2D is a pretty good library, so I don't see myself changing that. But yeah, we basically have this begin collision thing. And instead of calling this object B, I'm going to call this a colliding object. This is the contact, and this is the hit normal. Right, so this is the normal according to us, the hit, the direction of the hit. Right, and we're basically going to do the exact same thing, except we want end collision, right? We want to know when the collision is over, and a couple other ones that you may not be familiar with is pre-solve and post-solve. And these are other things that Box2D gives us, which are useful in certain scenarios, which we will find out later on in the series when we go to actually use these. Pre-solve is good for like one-way doors, so basically if you want to jump up through a block, but you want to have it solid on the top, this is very useful for that and for other scenarios, which we will see. Let's go back into Jade Contact Listener now. We can see that all the errors resolved here. And guess how easy it is for us to implement the other things? Well, it's so easy. We can just go paste, paste, and paste. Very nice, except we do want to change. This is now end collision. Make sure to fix that. Pre-solve is now pre-solve instead of that. Fix that, fix that. And post-solve is now post-solve. And fix that, fix that. And pre-solve and post-solve are called, so like what ends up happening, and you can read this in Box2D's documentation, pre-solve gets called, then it calls begin contact, and then it calls end contact, then it finally calls post-solve. So it's exactly what it sounds like. So that basically means that none of the impulses have been applied to the object. So in pre-solve, you could say, hey, actually, I don't want you to solve this. Say it's the one-way door. You're like, no, I want it to collide through this. Then you can tell it to stop solving for this, and then it'll stop. So we will actually do that later on. So that is our contact listener done. All right, very quickly, let's talk about raycasts. Raycasts are an important part of a physics engine and something that we will definitely want to add support for. So we will have a function that returns some raycast info, and we'll just call this raycast, and this will have a game object, the requesting object. So who is asking for the raycast? This could be null, and that is perfectly fine. Then we'll say vector 2f point 1 and vector 2f point 2. So this is basically the start of the raycast and where you want the raycast to end. Then what we can do is we can say raycast info callback equals a new raycast info requesting object. And you'll see why I called this a callback in just a second. The way Box2D implements this is kind of weird. I guess this is probably the easiest way he could have done it.
but it was confusing to me at first. What ends up happening is we say world.raycast, and you can see this takes in a callback, and we have to make a function that basically Box2D will call us once it finds the results. And we set it to our callback, and then we give it 0.1 and 0.2, and then we can say return callback. So let's go ahead and create another component inside of physics 2D, and we'll just go ahead and call this raycast info, okay? And this raycast info is going to implement raycast callback, okay? And we want to make sure to hit Alt Enter and just implement the method. So we get this one method, and if you read up on the documentation, he goes into extensive detail about how this works, which we'll talk a little bit about. So first of all, I'm gonna say this contains a fixture. So this will be the fixture that we hit. This contains a vector 2f point. This is the point that we hit, right? I guess we could call that the hit point. It doesn't matter too much. And then we've got a public vector 2f normal. This is the normal of the hit that we got. So what direction did we hit it at? Public float fraction. This is the fraction of the distance along the vector that we hit it. So 50% would be right in the middle of our 0.1 and 0.2. Public Boolean hit is something we'll have, which just tells us whether we did indeed hit something or whether it was unsuccessful and we hit nothing. And then game object. Requesting object is, as we talked about, just the object that was requesting for this callback, which could be null, perfectly fine. And actually, we want that to be private because the user doesn't care about this. But we will have one last thing, which is the game object, the hit object. So this is the object that we ended up hitting. Then you can see basically what we're going to want to do is just have a public raycast info. This takes in a game object, obj, and we'll just say fixture equals null, point equals new vector 2f. So we'll just sort of initialize everything to be nothing. We'll initialize the normal. The fraction is 0. We didn't really hit anything. Hit equals false. And then we'll say hit object equals null. This dot requesting object equals the object that they passed in. Then inside of here, this is the callback that fit Box2D calls. So what happens is inside of physics 2D, we say, hey, Box2D, we want you to send a raycast into the world. And real quick, this is bothering me. Change this to new vec2, and this should be 0.1.x, 0.1.y. Change this to new vec2, 0.2.x, 0.2.y. Okay, that's better. Anyway, so what happens is we say, hey, Box2D, send a raycast into the world, and I want you to call this function once you find it. Now, this is all happening synchronously. It's not like this is going off and doing something, and then the game engine just continues. No. What happens is we call this function, at least from what I can tell. Correct me if I'm wrong. We call this function. So Box2D goes and does some stuff, which I just clicked into it, which doesn't really help us much. Does some stuff, and then once it finally finds something, then it'll call our callback, right? So then it calls this function that we've implemented in our interface. If it doesn't find anything, it doesn't call anything, and that's why we initialize it here, everything to basically say we didn't hit something. But if it does, it calls this with this information. The fixture it hit, you can see it just says vec2, vec2.1, so it just initialized these to kind of not very helpful information. But this is basically the point we hit. This vector 2 is the normal, and you can see this all if you look at the documentation, and this float is the fraction, okay? And what we can say is if fixture.userData, so if we hit the requesting object, if we hit the requesting object, we don't want to return that because the game object doesn't care about that, right? The raycast, we want to see if we hit something other than the person who's requesting it. So what we can do is we can say return 1, which if we return this, Box2D will continue looking. So this is why he implemented it as a callback, because what happens is we say, we don't really want this one. Keep going and see if you find anything else. And then Box2D continues to go. Then if it finds something else, it calls this again. And then what we can do is say, if it wasn't that, then we can say, oh, cool. Well, this fixture equals the fixture. This point equals a new vector 2f, point.x, point.y. This normal equals a new vector 2f, normal.x, normal.y. This fraction equals the fraction. And this hit equals fraction does not equal 0. If the fraction is 0, that means we did not hit anything. I don't think we ever actually encountered that, but it's good to have that just in case. This dot hit object equals game object var or fixture dot user data. So we basically just set that. And then what we can return is the fraction. And if we return the fraction, then that tells Box2D, okay, we're done now, you can stop. If we return fraction or 0, I believe, it basically just signals this to stop and it will stop. And I may be misquoting that a little bit. If you return fraction, what it'll actually do is it continues to go. And if it hits any other objects, it'll return those as well, which is kind of weird. We won't go into that. That's a little bit more complicated. So just think of this as it could be any one of the objects within the raycast. This is not necessarily the first object the raycast hit. This could be any object within the raycast length. So keep that in mind. If you want to make this a little bit better, look at the documentation. It'll help. But yeah, that should be good though. And if we go back into Physics 2D, you can see that our raycast should work fine. And we now have a way to raycast into our world. Now let's go ahead and let's fix up our Physics 2D class a little bit more because I do want to abstract this stuff out real quickly. Very quickly, let's go up to the body definition. We will be adding a couple more things to our rigid bodies that will be useful. One of these will be gravity scale. So we'll say rb.gravity scale. And then we will also be adding in angular velocity, which I don't believe we have. Yeah. So we'll be adding both of these in just so that you can set these values if you want to as well. And then one other thing we will want to do is right here, after we create the body, we actually want to set the mass. So we'll say body.mass equals rb.getMass. And I'm not sure if it matters when you do this stuff, but this is the order I've done it and it works this way. So I would recommend following a pretty close ordering to this. Okay, and then we'll actually get this circle collider working correctly. So instead of doing this, what we're going to say is add circle collider, and we're going to create another function that's helpful, and we'll give it the RB and the circle collider. So we'll go ahead and create this function right below Box2D collider. So we'll say public void add circle collider, and this just takes in a rigid body, RB, and a circle collider. Circle collider. Then we will simply say body equals rb.getRawBody. Basically, we're going to be doing something very similar to all of this. So I'm just going to copy that, paste it. And instead of doing polygon shape, we're just going to have a circle shape. So let's say circle shape equals new circle shape. Then we can get rid of most of this. We'll go up to there. And we'll say shape.setRadius to circle collider.getRadius. And we'll say shape.mp, which this was kind of hard to figure out, but basically that's the offset. So it's similar to our Box2D's offset except for circles. And we'll say this is set to circle collider.getOffset.x, circle collider.getOffset.y, and that should be good. And then we've got the fixture def. Fixture def should be mostly the same. Except user data is now a circle collider.gameObject, and everything else should be good. I'm going to remove these, that way we go ahead and actually implement these. Okay, and we're going to add a couple more useful functions which we will be using as well, which is public void reset circle collider. This will take in a rigid body, RB, and a circle collider. And this is simply going to reset all the colliders to this new circle collider. So we'll say body equals rb.getRawBody. If body equals null, we will return because there are no colliders and there's not a physics object really. Then we're going to say int size equals fixture list size body. And fixture list size is a function that we will create, which will basically get us the number of fixtures. So we'll just go down here and we'll say private int fixture list size, which takes in a body, Box2D body. And this will say size equals 0. Fixture equals body.getFixtureList, which will get us the first fixture in this singly linked list. And we'll say while fixture does not equal null, size ++ fixture equals fixture.next, which should just iterate through that list. And then we can return the size until we hit the end of the list. So that's how we'll get the size. And once we get the size, we're just going to say for int I equals 0 until I is less than size, I ++, and we'll say body.destroy fixture, body.getFixtureList, which should just destroy all of the fixtures we have in there, and I'm missing a semicolon. And then we're going to say add circle collider after we do all that, RB circle collider, and we will want to reset the mass data since we've changed a collider. And we're going to do something very similar except for box colliders. And I guess I should have put that above circle colliders, but it doesn't matter. So we'll say reset Box2D collider, and this will take in a Box2D collider.
We'll call this box collider. And we'll simply change this to that, and we'll say add box collider. And yes, I know there's a lot of repetition and everything in here, but it works and it's not too much of a hassle for me. Ideally, you'd probably want to abstract this into its own function just to make sure you're not repeating yourself like I am here. These are helper functions that we will be using in the future, but for now, it's fine. Now, we want to add in friction, is sensor, all these things to our rigid body. So let's go ahead and go into our rigid body very quickly. And we're going to go ahead and say private float friction, which is a value we'll want. I'll just initialize it to 0.1, doesn't matter too much. Public float angular velocity equals 0. And I chose public and private for these just because I was getting lazy and didn't want to make these private anymore. I really don't care too much in this case. So you can make these all private if you want to be super safe. They'll say public float gravity scale equals 1.0f. So gravity is just normal box 2D gravity initially. And then we'll say private boolean is sensor equals false. So it is, oh, and a sensor too. What is a sensor? Well, a sensor is basically like a dynamic object in the world that doesn't actually affect anything. So it doesn't collide with anything, but it still calls begin collision, end collision, all that stuff. It just doesn't actually bounce off of the things. So that's all a sensor is. And they're useful if you want like a trigger or something. You could just make it a sensor and it's a trigger now. It triggers when things enter into it. So that is good to have. And we will of course want some helper functions here. So we'll say public vector or void add velocity, which takes in a vector2f force to add. So I guess this should be called force, but it's fine. And we'll say raw body dot apply force to center, new vec2 velocity dot x velocity dot y, which should add a velocity. And we'll say if raw body does not equal null, just to be safe, because we don't want to apply that on accident. So we can add the velocity. We will also add a way to add an impulse. So let's say public void add impulse. Oh, and that's actually what I did here. So whoopsie. So this will be impulse. And we will do this inside of add impulse. For this one, we want to apply or add a force, which I think is just, okay, yeah, apply force. And the point we want to apply this to is the raw body dot get center, I believe. Let me just double check. We should actually be able to just say apply force to center here. Get rid of this. And for the impulse, we will want to say raw body dot get world center. Okay, there we go. That way we just add it to the center of the objects and give it a little bit easier for our users of our engine. They don't have to think about that stuff. They just say add impulse and don't have to think about where it's adding it to. Inside of set velocity, we're just going to change this to dot set velocity. And then we'll say if raw body does not equal null, then this dot raw body dot set linear velocity to a new vec2 velocity.x, velocity.y. So we're just adding it to the raw body as well as our thing to keep track of it. And then inside of angular velocity, well, we don't have that yet. So we'll add that right here. We'll say public void set angular velocity, and this will just take in a float. And the reason angular velocity is one dimension instead of two dimensions is because that's how angular velocity works. If you think about it, it's only spinning on one axis, which is the z-axis, whereas linear velocity is a two-dimensional force. And we'll just say if raw body does not equal null, this dot raw body dot add angular, or I'm sorry, set angular velocity to that guy. And we'll also want to do this for gravity scale. So we'll say set gravity scale, right? Just a lot of helper functions to make our lives easier once we actually start coding this game. So we'll say set the gravity scale. And then we'll say this dot gravity scale equals gravity scale, and then we'll say set gravity scale to this, and we should be good. And then we'll add another function. This will be public void set is sensor. So this will just set it to be a sensor. So we'll say that's equal to true. We'll say if raw body does not equal null, then window dot get physics, which is something we will also add too. So we'll say window, import that, dot get physics, which we don't have. We will add that in fiction in a second. And then we'll say set is sensor to true. And we'll say public boolean is sensor. And this will just return this dot is sensor. And we'll have one more, public void set not sensor, which will set it to be not a sensor. So we'll say is sensor equals false. If raw body does not equal null, then window.getPhysics.set not sensor. Oh, and this should be this, not true. So we're just gonna do this over here as well. Okay, and that should be good. We just need to go to our window real quickly and we'll add in a function, which is just public static physics 2D get physics, which will return get.current scene dot get physics. Should be good. And then we will go ahead and let's see what's wrong with this. Oh, and this is IntelliJ is just warning me about this. We don't need to access this via get. We can just say current scene since current scene is static. So I'll fix that real quickly. And then we'll just go to current scene. We'll go into scene and then we'll add in a public void get physics, which should just return this dot physics. Okay, and then if we go back into window, that should be good. No errors. Nope, I do have an error. Physics, get physics inside a scene should return physics 2D. Whoopsie. Okay, then if we go into window, window's good. If we go back into physics, or I'm sorry, rigid body, we will have another error because we don't have set not sensor and set is sensor. So let's go back into physics 2D, and I promise this should be the last physicsy thing we have to do today. And we can go up here and we can just say public void set is sensor. And we will take in a rigid body and we'll say body equals rb.get raw body. If body equals null, we'll return because we can't really do anything. And then we'll say fixture equals body.get fixture list because we actually set the sensors on a fixture basis. And if we want to set it on the whole raw body, then we have to go through all of them. So we'll say fixture.mSensor equals true and fixture equals fixture.mNext. Should be good. And then we will add in set not sensor. If we go ahead and just copy that, set not sensor, and we'll just change that to false. And if we compile, we are not out of the woods yet. Let's go into rigid body and add in get friction. So we'll just say public float get friction return this dot friction. Okay, if we go and run this one more time, there we go. Now we can run it and we should be able to add objects. We can select multiple objects at a time. We can duplicate those objects if we want to. We can go ahead and add Mario if we really want to. Deselect objects just by clicking off of them. We can play, stop the scene. As you can see, we are getting closer and closer to a full engine. In the next episode, we will be getting much closer to what I have here. So we'll probably have to add in pillbox colliders, which is what I have on Mario here. And we'll start coding Mario. We should be at a good place. And you can see I've tweaked it a little bit more because I didn't quite like the way the controls were working. So we'll be learning about how to like basically code the whole game. Add in vario length jump times. You can see that I can jump small or big if I want to. These blocks all work. We can pop out a mushroom. We can grow into Big Mario. If we hit a bad guy, if I fail. Let's see. I get hurt and then I get invincible for a little bit. And then if I hit him again, I die. So we'll be adding all this stuff. It's a fully working game. I still have a couple things left to implement, but I'll get those done. And then we'll basically just build this. All right. So I hope you guys are looking forward to that. And I will see you in the next tutorial when we actually start implementing the game. In this episode, we're going to be implementing the pillbox collider you see on Mario here, and we will be implementing the player controller. So that will be pretty cool. Now, just as a reminder, or I guess sort of I'll show you guys, I've gone ahead and implemented a little bit more of the game. So it's basically complete now. You can go ahead and you can go and get your power-ups and everything, and you can play pretty much like a normal game of Mario. You can go through the pipes now. They all work. There's no coins here because I figure I'll leave that up to you guys. If you really want me to, I can implement them and then we can go over them in the series, but it's simple enough. Fire Mario works and everything too. And then you hit the flagpole and you slide down. He slides down the wrong way and everything, which I realized afterwards, but you know, it's good enough. And then it changes the scene back to the level editor once you finish up. So we've basically got a fully working game. And you'll notice that as I zoom out, you can sort of see the whole level in context, which is pretty cool. So this is what we're working towards, okay? Just another reminder. And we will be implementing the player controller, which is not as easy as you might think. All right, so before we go ahead and actually build Mario, we need to go ahead and add in that pillbox collider that I showed you. And even more important, I guess, we should very quickly actually set up our physics to support those contact listeners we set up last time, right? So I went about setting up the contact listeners and everything and completely forgot to show you how to actually set it up so that the contact listeners work. It's very simple. I just completely missed that step. So if we go and make a constructor in our physics 2D, you can tell physics or box 2D to call back to your contact listener by just saying, hey, world.set contact listener to a new Jade contact listener, or whatever you called yours. And that's all you need to do. This will basically just set it so that now whenever we get those begin and collision callbacks and all that stuff, it will go through our Jade contact listener like we want it to. With that out of the way though, let's go ahead and go into the pillbox collider, because that is a little bit more complex, but it's still not too bad. So I'm going to go ahead and create a new component here. We will just call this pillbox collider. And this is going to be exactly that. And I guess this is a good point too. I should probably explain why I have a pillbox collider. So I initially tried setting up Mario as an actual physics-based solution. I originally coded it so that was using box 2D physics to basically control the player input, but it didn't work out too well. The controls weren't as snappy as I would have liked them to be. Mario didn't really accelerate the way I wanted him to, and I couldn't get it to feel quite right. And I looked it up, and the common theme is basically to use the physics engine to handle collisions and stuff, but you can basically you set the velocity yourself and sort of set the rules of your player control yourself. That way you can get fine-tuned control over it while still having the advantage of the physics engine. Now, of course, not all games do that, but it is a pretty good way to handle this, and it worked so much better for me. And I used a pillbox collider because as you're sliding over boxes, it's really easy to catch onto one of the boxes on accident. So like if we go back into the scene, we have all these boxes down here, and it's very easy if Mario has a box collider attached to him for it to catch onto one of these corners. And if you switch to a pillbox collider, that just makes sure that you don't. So it's a good thing to have in an engine, regardless of what you're using it for. And it's not too hard to implement. So the way we're going to implement it is we'll say we have a private transient circle collider, top circle. So this will basically be the top circle in the pillbox, right? And the pillbox, I should probably explain this too. A pillbox collider is basically just it looks like a pill, right? So you can see Mario here, and you can see that Mario sort of has these two circles on here, and there's actually a box in here too, which is a little bit harder to see, but you can see there's a box in between them, and that box sort of represents, if it was to get taller, then the box would basically represent the height of Mario. So that's the pillbox collider, and that's what we're creating here. So we just need two circles and a box for the center. So let's say private transient circle collider bottom circle equals a new circle collider, and then we'll go ahead and say private transient box collider 2D, and this is our box is a new box 2D collider. Okay, and then we're going to go ahead and say private transient boolean reset fixture next frame, and this is something I added in a little bit later into the game engine. Basically what this means is I had the use case, right? So let me show you exactly why we have this. Basically, when you're Mario, you have a small box collider because you're little Mario, right? But as soon as you hit this mushroom, you grow into a bigger Mario and your hitbox changes. And so I literally have to change the size of the hitbox. But since we're doing that on a collision, you can't just change the size of a hitbox in the middle of a collision, right? So what we have to do is we have to basically cache it and say, okay, at the end of this frame, we want to reset this because we've changed some details about it. And that's basically what this flag is for. And then we'll go ahead and say public float width. So this is the width of it. And I just initialize that to 0.1, which is going to be Mario's like base height, I think. And then we'll say height equals 0.2f. It might not be, it might just be random numbers I chose. And then we'll have public vector 2f offset equals new vector 2f. So that will just be the offset. And the reason I'm not making this extend from component or box some collider, I think. Yeah, we have this collider and it has the offset. I got rid of this because basically when you inherit stuff, you can't really expose that in the properties window. So instead of doing this, we can actually do this right now. I'll just move this into the circle collider itself, and then we'll remove it from here, and we'll copy this, paste it into the circle collider itself, because it just makes things so much simpler. And then we're going to do the same thing to our box 2D collider. So we'll say private vector 2f offset equals new vector 2f.
And then we'll just copy that function too. And then we're going to get rid of collider, say this extends component now, do the same thing in circle, component, and now we can just get rid of collider completely. So if I just delete this, we should be fine. Okay, good. So now these are completely separated from each other, which is good because we can also expose these variables inside the editor like we want to. Okay, then we're going to go ahead and say override the start method. And on start, we're just going to say this .top circle .game object equals this .game object. So basically, these colliders aren't actually visible in the game engine. They're not like their own individual game objects. They're all sort of a combo. So this pillbox collider is like a combination collider, and you don't really care about the details of the individual colliders. You just care about these. So we don't really add these to the game engine itself. We just add them to this guy, which makes sure that they're only visible inside of here. They'll say this bottom, and that's also why we have to do this so that we actually assign our references and make sure that they're set inside the middle of the game. And then we'll say this .box.game object equals this .game object. Then we're going to say recalculate colliders, which is basically just going to figure out how big to make the circles based on the width and the height, and how big to make the box. Inside of public void recalculate colliders, we're going to say float circle radius equals width over 4, which should give us half of a half width, which is what we want. And then we're going to say float box height equals height minus 2 times circle radius. And then we're going to go ahead and say top circle dot set radius, circle radius, bottom circle dot set radius, circle radius, top circle dot set offset. And this is where it gets kind of interesting. So we're going to say set offset, and we need to add that function. So we'll basically go into here and we'll say public void set offset. This will take in a vector 2f new offset, this dot offset dot set new offset. And that should be good. Then we can go back into our pillbox collider, which I put in the wrong place too. We should put this inside of components. So you can go ahead and move that. That should be fine. Okay, so anyways, we will go ahead and say set offset, and we need new vector 2f. Well, where do we put the circle? What's the offset? Well, the offset is basically just this offset. So we'll get this offset in a new vector, plus 0 plus the box height over 4.0f. So what this is basically saying is we want to move the top circle up half of our, a quarter of our height. That way we make sure that our overall height will be the same, and they should basically align perfectly with the box's edges, okay? That might not make complete sense, but that is what the goal here is. Okay, and then bottom circle is going to be very similar. We're just going to set the new offset to new vector 2f offset dot sub 0 box height over 4. So it's mirrored just the other way. And then we're going to say box dot set half size new vector 2f width over 2, which is just sort of the way our game engine works. And the height should be box height over 2, and that should be good. Then we can just say box dot set offset to this offset, which I believe we have not added there either. So let's go ahead, copy this set offset function, and we'll just copy it into here. Okay, cool. And that should be good for recalculate colliders. Okay. Next, we're just gonna make a couple of getter functions. So I'm just gonna say code generate, and then we're gonna say getters, and we want to do these, and that should be good. So we just create some getters for those, and then we're going to create a function to help us to reset the fixture. So we're going to call this reset fixture, and we'll basically call this whenever we need to reset the fixtures. And so we'll say if window.getPhysics.isLocked, which we haven't implemented, but is very simple. This basically just means that we can't access the physics right now, so we shouldn't be changing anything. We'll just say reset fixture next frame equals true. So basically, if we're not allowed to touch the physics, we won't. Otherwise, we'll say reset fixture next frame equals false. And then we'll say if game object does not equal null, then rigid body 2D RB equals game object dot get component rigid body 2D dot class. And then we'll say if RB is not null, then window dot get physics dot reset pillbox collider, which we don't have yet, but we will add, and we'll give it the rigid body, and we'll give it this. So that's going to be very similar to the other collider function things that we have in the physics engine, and we'll be adding those. Let's go ahead and implement those really quickly. So we'll go into physics 2D, The isLocked one is pretty simple because we're just returning something that's coming from box2D. So we'll just say isLocked, return mworld, or world, I think we called it .isLocked. Okay, that should be good. And then for the reset box2D collider, I'm going to copy these two functions because it's going to be very similar. And then I'm just going to go ahead and do that. And then we're going to say add pillbox collider. And then this is going to take in a pillbox collider instead. And we'll just change that to PB. And then we're going to change this to reset pillbox collider. That's a pillbox collider, PB. And so this one is basically just going to say pretty much the exact same thing. And then down here, we're going to say add pillbox collider, and we're just going to give it PB and reset the mass data. That should be good. Okay, and then inside of pillbox collider, instead of doing all that stuff, we'll just take all that out, and then we're going to say add box2D collider, RB, and then we'll say pb.getBox. And then we'll say add circle collider, and we'll say RB, and then pb.getTop circle, and add circle collider, RB, pb.getBottom circle. Okay, and we should be good now. That should add all of them back. So we should be good with everything there. Let's go back to pillbox collider. All of those errors get removed. Then we're going to go up here. We just want a couple more helper methods. Public void set width. And we obviously want a new value for that width. Then we'll just say this dot width equals new val. And we'll recalculate the colliders. And then we'll just have reset fixture. Okay, and that should be good. And we'll do something very similar for set height. We'll say set height float new val this dot height equals new val. Recalculate the colliders. Since we changed the hitbox, we need to reset our fixture once again. And if needed, this will reset the fixture on the next frame, which should be good. Then we're going to go up here and we're just going to say at override public void update float delta time. And we'll say if reset fixture next frame, reset fixture. So that's how we keep track of it. We'll just keep trying to reset it until it actually succeeds. And then inside of at override public void editor update float delta time, we're going to say top circle dot editor update dt, bottom circle dot editor update. This way we can just see the green lines being drawn and stuff. If we add debug drawing, which I don't know if we have or not, but we can add that if we really want to. And then we'll say if reset fixture next frame, reset fixture. So we just do the same thing in debug mode. That way it gets set properly every time. Okay, cool. That took a little bit longer than I was expecting, but that is pillbox colliders. Now we actually want to start implementing our player controller. And in order to do that, we need to create a prefab for Mario. So if we go ahead and go to our prefabs class, we already have one for Mario, but we're going to be adding a lot more. So I just have one animation state here, and I'm not going to spend the time to type out all this stuff because the way we have our animation state set up right now, it works, but it's really hard. It's not hard to code. It's just time consuming. And I am not going to retype all this. So I'm just going to copy all of the state machine stuff, and then I'm going to show you guys what I did just so that you can see that. So basically, I'm just going to replace this right here with all of Mario states. And you'll see why I did not do this in just a second. So basically, this is all the code we need. And also, we need another sprite sheet. So I'm going to go ahead and paste this in. This is basically just the big player sprites. And if we go back to level editor scene real quick, and we'll come back to this, don't worry. We basically want one more sprite sheet in here, level editor scene initializer inside of our load method. Here we go. And I'm just going to add some things. So I'm just going to copy and paste over this too. This is just adding a few more sprite sheets. There is nothing special about this. I'm just loading some other pictures I have, which will also be in the documentation or in the GitHub link if you want to download these images and follow along. And you can even copy this code too if you don't want to type it out. But basically, I've just added a few more sprite sheets. We have one for the turtle, one for big sprites. So that's like Mario when he's 32 by 16 pixels. And then one for all the different pipes and one for special items. So that is that. And then if we go back into prefabs, I have just loaded the big sprites because Mario needs those sprites. And then basically what we've got here is just a bunch of animation. So I've got the run animation, which default frame time is 0.2. And then I just basically select all the sprites that we need for that and then set it looping to true. Then I've got the switch direction is basically when Mario's running and then he changes directions. Idle is just him standing still. Jump is him jumping. Then we have the same thing for his big state, right? So when he's big Mario, okay, same thing. Then we have the same thing for when he's Fire Mario, okay? So just same thing again. which is why I'm not going to go through all this. Okay, then we get the state machine. I add all the states to the state machine, right? So run, idle, switch direction, jump, die. Die is the only other animation frame I had, which is basically just his death animation, which is just a single frame. Then I add all the big animations, and then I add all the fire animations, okay? So if you want to use the state machine, this is how you use it. You just set up the different animations. You add them all to the state machine so that the state machine knows about them. Then you have to add all the transfers, okay? This is where it basically gets pretty complicated, right? So we say we want the default animation to be his idle, right? That's the default animation. Then we add a transfer from when he's running to switch direction on trigger switch direction. We go from running to idle on stop running. We go from running to jumping when you trigger jump. Switch to idle when you say stop running. Switch to run when you say start running. So basically we're just going and hooking up all the different animations. Like you go to this when I give you this trigger. And we have to go and then repeat that for all the big directions. And then we have to do that for Fire Mario, basically the same thing. And you'll notice I'm using the same triggers here too. So like jump, jump. That way when we're coding, we just have to say on jump, we just trigger jump. And it doesn't matter what animation Mario is in, he will always go to the correct next animation, which is sort of why this is useful. Then we have a power up animation, which basically just makes sure that he powers up to the appropriate next one. So if he's on Little Mario, he goes to Big Mario. If he's on Big Mario, he goes to Fire Mario, no matter which state he's in. Then we have damage, which basically goes the opposite. If he's big, he goes to little. If he's fire, he goes to big, no matter which animation he's in. And then we have the die animation, which basically just goes from all the animation states to die on trigger die. Okay. And then we add the state machine. So it's a lot of stuff, but it's really, there's nothing complicated, just a lot of code. Next, we want to add a pillbox collider to him. So we'll say this is a new pillbox collider. And we're going to say pv.width equals 0.39f. These are the values I found that worked the best for me. And then we'll say 0.31f. Then we're going to say rigid body RB equals a new rigid body because we want to add a rigid body to Mario 2. And we'll say RB.set body type. This is going to be a dynamic body since Mario will be moving. And then we're going to say RB.set friction. Actually, friction doesn't really matter because we're not going to be using that. So I'm going to ignore that. Continuous collision, though, I'm going to set that to false. I think I have it as true by default, and I guess it should be false by default because Mario is not moving. You only want continuous collision if you're using something that's going to be going at very high speeds, which Mario shouldn't. Then we're going to say set fixed rotation to true. We don't want him to topple over whenever he hits anything. And then we're going to set the mass, which again, since we're going to be handling physics ourselves, sort of, this doesn't really matter too much, but that is what I had it when I was actually using physics. Okay, then we're just going to say add component, RB, add component, PB, and add component, a new player controller. And this is where the fun begins, okay? So we don't have a player controller yet, but we will generate that. And we can just return Mario. So let's go ahead and create a new component. And we're just going to call this player controller. And this is going to be a big class, okay? This is not necessarily the way I would write it if you wanted super clean code, but it works. We need player controller, and I spelled that wrong. That's why it's not showing up. Okay, there we go. So if we run this, we're going to get an error. It's because I haven't copied my new images. So if you're following along with this, make sure to copy the new images that I loaded into your appropriate directory. Okay, now if we run this, we get it opened up successfully. Now, one thing that you'll have to remember is every time you change a prefab, it's not going to update automatically in the game. You'll have to delete whatever objects you use that, then re-add them. That's not the best, but it's the only way we can really do that right now. And we got an error, so let's see what this is saying. Okay, this is another good important point that I forgot about. So we get this error, and it looks really weird. It says JSON syntax exception. You can see that it's coming from Gson, and if you were like me, you're probably like, what the heck? What's going wrong? My first thought was, okay, this must be the state machine, because this is the first time I've tried to copy the state machine. And sure enough, it is the state machine. And if you look in the state machine, we actually have this hash map, okay? And we want this hash map to be serialized, but for some reason, Gson doesn't like hash maps with complex objects, like this state trigger that we're using, unless you go into our scene, and then we scroll all the way down to where we serialize things, and
we add in this line that says .enable complex map key serialization. I don't know why they don't have this enabled by default, because I think most people probably want this enabled by default, but basically this just says, okay, now you can use it and it won't, break on you. And we just need to make sure to put this everywhere we create a Gson object. This is probably where it'd be nice to have like a global Gson object with our settings that we prefer, but that's some improvement you can make down the road. I think the last place we want to add this is inside the game object, because inside our copy method, yeah, we have this right here too. So I'll add that in there. Then if we go back in, we should be able to, first of all, delete Mario. Then we'll go ahead and add him. And there we go. We click him and we add him in and we get no errors. One other thing, our circles are not drawing, and that's just because we need to add our circles. And he's falling. That's great because he has his box collider, or his colliders. Let's add in debug drawing for the circles just so that we can see those. So let's go to circle collider real quickly. And then we're just going to go ahead and say @override public void editor update float dt. And we're just going to say vector2f center equals new vector2f this dot game object dot position, or dot transform dot position dot add this dot offset. So that's basically where the center is. And then we're just going to say debug draw dot add circle and center this dot radius. Okay, that way we can actually see what we are doing, and we should be able to run this. And now we should see Mario actually has those circles. There we go. Yep. So Mario's got the circles. He is working all right. We don't have any box colliders on these boxes though, so that would be useful. So let's go back into our level editor scene initializer. And the way I did this was basically just by modifying this loop where we can click to get new items. So be prepared, because I just sort of went through the sprite sheet and found the sprites I wanted to have box colliders and manually did stuff to make it work. So instead of going, well, okay, yeah. So right here, I basically just said if I equals 34, continue. So this is a sprite I don't want to have a box collider. And I say if I is greater than or equal to 38 and I is less than 61, continue. So I'm basically just skipping all the sprites that I don't want to have box colliders. Then what we're going to do is we're just going to say right here, when we create the game object, we will say rigid body 2D RB equals new rigid body. And we're just going to say rb.setBodyType. And then we're going to go ahead and say bodyType.static, because these are going to be immovable objects and static is the appropriate thing in that case. And we'll say object.addComponent RB. And then we're going to say box2D collider. B2D equals new box 2D collider. And I've also made sure that all of these blocks, I believe, are the grid width. So we can safely say set the half size to 0.25f, 0.25f, and that should be good. And I'm just going to add that to the object as well. So we'll add B2D. And we're also going to add a new component, which is ground. And that way we also know that these are all ground components. We'll just go ahead and create a new class in here. Call it ground. That is good. Extends component. And this is basically just going to be a data only thing. It's not even going to have data. It's just sort of a tag. It's like, hey, this is ground. Okay. That's all we're going to use it for. So if we go back into level editor scene initializer, you can see that we're good here. This needs to be a vector2f. And then for breakable bricks, because those are a thing too, we'll say if I equals 12, which is the one that I wanted to be breakable brick, we'll say object.addComponent new breakable brick, which we don't have yet, and I'm not going to be doing in this episode anyway, so we'll just comment that out for now. Okay, so basically now if I go ahead and I'm going to delete all of these, and then if we click it now and we add it, you can see it's got green because we are adding box colliders too. So now if we run this, Mario shouldn't fall through them. And that makes sense. I was just not thinking, and we never added in a case to handle pillbox colliders inside of our physics. So if you go into physics 2D here inside of our add game object method, we just basically need to make sure we actually add the pillbox collider if you have it. So say if pillbox collider equals go.getComponent pillbox collider.class does not equal null, then we'll say add pillbox collider RB pillbox collider. Hopefully this should take care of it. I'm not actually sure. I put in another Mario because I was testing some things. So now if we play it, okay, yeah, now he hits the ground and he actually stays on the ground. Cool. So that's good. Let's make him move. So let's go into player controller and actually start implementing a player controller, which, like I said just a second ago, is a lot harder than you might think it is to make it feel right. This is going to be a giant class too. I'm just going to say that up front. So I'm going to say we're going to have a float walk speed, and this is his walk speed initially, and then public float jump boost, or basically this isn't his speed, but like the force we add every frame. Jump boost will be 1.0, public float jump impulse, and these are just the values I found that work the best, is 3.0, and then public float slow down force equals 0.05f, which is sort of like friction, the way I did it. And then this is where we sort of have to implement our own physics a little bit. So we'll say terminal velocity, which is the fastest he can go, is a new vector 2f. 2.1f, 3.1f, which are good values that I found. And then we'll say private, or we'll say public transient Boolean on ground equals false initially, because we don't know if he's on ground or not. And then we're going to say private transient float ground debounce. So this is where it's just a massive amount of variables that we need to keep track of a bunch of different state about the player. So we have a ground debounce, which basically says this is how much time you have that you can hold the space button after you've pressed it. Because otherwise we don't want you pressing the space bar anymore. That way you can have a variable length jump, okay? And then we're going to say private transient float ground debounce time, which is basically like how much time you get each time, which is like 0.1 seconds for jump. Then we're going to say private transient rigid body 2D, RB. So this is basically the rigid body attached to this game object. We also need the state machines that we can switch states. We also want to have a float big jump boost factor. So basically when you switch sizes, Mario needs to jump a little bit higher for whatever reason. So when he's bigger, it's because his mass data changes. I was using this for the initial physics. We might actually not need this anymore, but I'm keeping it here because I have it. And then we also need the player width, which I'm going to say is 0.25f. And then we also need the jump time. Okay, so this is basically how long we've been, how long we have left to hold the spacebar. So actually, ground debounce, I was a little bit wrong. So ground debounce is basically if you run off a block, how much longer do you have to hold it? So it's like a little bit of a grace period. So if I pull this back up again, you'll notice that I can run off the edge of a block and I can still jump off of it if I don't die. So if I go ahead, that lag is messing me up. Okay. So if I jump up here or up here, I can jump, and then as I am on the edge of the block, I have 0.1 seconds to basically still jump. Okay, you see I just ran off the edge there and I was still able to jump. So that's what the ground debounce time is. It's basically saying I have 0.1 seconds to basically press jump key, which gives me a little bit more leeway, and it's noticeable, trust me. And then jump time is basically if I'm pressing and holding spacebar, how long have I been holding it? That way we can adjust it for a variable length jump. Then we're going to have a private transient vector 2f acceleration, okay? And we're going to do this, and then we're going to say private transient vector 2f velocity equals a new vector 2f. Then we're going to say private transient Boolean is dead. And we're not going to be implementing all this today. These are just so that we have them later. And then private transient int enemy bounce equals 0. That's basically when you're jumping off an enemy. And that is all I will have for now. Okay. So then we're going to do public void start. So on start, we want to make sure we get a hold of the rigid body attached to our game object. So we'll say get component rigid body class. We also want state machine equals game object dot get component state machine dot class. We also want our to set our gravity scale. So we'll say rb.set gravity scale, which we haven't made. So we'll make that in just a second to 0.0f. Let's go ahead and implement that real quick. So if we just go into rigid body, wait, we do have this. Oh, I imported the wrong rigid body again. Okay, so get rid of that. And then I'll hit Alt Enter and import it from the correct package. There we go. So then we can do that. This should be state machine.class. And we're setting the gravity scale to 0 here just because we don't want to be letting Box2D. The Box2D is not going to control our physics. We are controlling the velocities ourselves. That way we can get fine-tuned controls over how it feels. Then we're going to have our update method. So let's start with the simplest thing, walking, right? We want him to walk. So if keyListener.isKeyPressed, GLFW key right, or keyListener.isKeyPressed, GLFW key D. So if they're pressing the right arrow key or D, we're going to say this.gameObject.transform.scale.x equals player width. So basically we're just going to make sure that we're facing in the right direction. We're going to say this.acceleration.x equals walk speed. So I guess that should be walk acceleration. And we're going to say if this.velocity.x is less than 0. So if we're moving to the left and they're pressing the right key, then we should play the switch direction. So we're going to say trigger switch direction, which should basically make Mario look like he's trying to turn back to stop himself. And we'll say this.velocity.x plus equals slowdown force, which will basically make us slow down in a linear sort of way. And then we'll say otherwise, we'll say state machine.trigger start running. And we're going to copy this because it's essentially the same, except if we're pressing the left key. So we'll say GLFW key left, or if we're pressing the A key. So key A. And if that's true, we want to set our scale to negative player width so that he's facing to the left. We want to set our speed to negative speed. And then we want to check and see if the speed is greater than 0. So if he's going right and, we want to slow and he's trying to slow down, we're going to subtract the slowdown force so he slows down linearly. We're going to switch direction. Otherwise, we will trigger state machine. So if we run this as it is now, we should be able to run right and left. Almost. We're very close. You can see that he's sort of moving directions. He's changing, but he's not moving because we're not actually setting the velocity ourselves yet. So the last thing we need to do is basically tell Box2D, hey, this is the velocity we're running at. So we can say this.velocity.x plus equals this.acceleration.x times dt. This.velocity.y plus equals this.acceleration.y times dt. So we basically set both of those. And then we'll say this.velocity.x equals math.max, math.min, this.velocity.x, this.terminal velocity, and then I think negative this.terminal velocity.x. This should be .x as well. So basically what we're doing is we're just saying this is a clamp function. We're basically saying use x or clamp it to the negative terminal velocity or the positive, whichever it's in that range. That way we don't ever go above our terminal velocity, which is how terminal velocity works. So we'll do the same thing for y. We'll say this.velocity.y, this.terminal velocity.y, negative this.terminal velocity.y. Okay, so that should ensure that our velocities get set appropriately. That will add to our velocity, but we still haven't told Box2D about that, so we need to say this.rb.setVelocity, this.velocity, and this.rb.set angular velocity to 0. That way we just aren't twisting or doing anything weird like that. So if we do this, we should be able to run to the right, to the left. He's not slowing down because we haven't added friction, but you can see that it works pretty good. He's also not animating correctly, so we'll have to figure out what's wrong with that. And he is also not falling. So we'll just say for now, this.acceleration.y equals window.getPhysics.getGravity, which will add .y times 0.7f. So I'm basically just going to use Box2D's gravity, 70% of Box2D's gravity, which felt pretty good to me. So we'll just go into physics real quickly, and then we'll add in public vector 2f get gravity, return this dot world dot m or get gravity, and we just want to convert this to a vector 2f. So we'll say new vector 2f. We'll say .x and then world.getGravity.y. Okay, and I'll remove this here. Go back to player controller. So that should at least make sure that we're falling, but we're not actually going to stop. So yeah, because if we do this, we're just going to, actually we might stop. So if we do this, okay, yeah, so the ground still stops us, which is good. You'll see it's a little bumpy because we're basically getting hit into the ground. What we want to do ideally is if we're hitting the ground, set the acceleration to 0 so that
we kind of glide across it instead of hitting it and sort of encountering that force. So you can see that even though we're implementing these velocities and stuff, Box2D is still doing a lot for us because it's handling those collisions, which would be super hard if we weren't using it. Oh, and you know why the state machine trigger isn't working? It's because I implemented this kind of stupidly too. So I saw this and didn't even faze me. Like IntelliJ is warning me about something here. It says list animation state may not contain objects of type string. So what this is telling me is, hey, you're using this index of function, but this isn't actually going to get you what you want. So instead of doing that, we're going to say state index equals state index of, and then I'm going to do instead of this, that. So we're basically going to create this function that sort of does this for us, right? And so I'll go ahead and say implement. I'll say create method, and this is going to return an int, and it's going to take in a string. So yeah, that's good for me. Just let IntelliJ do that. And what we're going to do in here is we're just going to say int index equals 0 for animation state, and states. We're basically going to look for the state machine matching this S, which is really the state title. So we're just going to find the one that matches that. We'll say if state.title.equals state title, return index, and then we'll do index plus plus here. Otherwise, return -1. So we basically just loop through, find the correct one, and then return that correct one. So now, if we run this, we should see him switch states. Yeah, okay, there we go. So now we get Mario, and you'll see that he goes into the switch direction mode when we're switching directions, which is cool, right? We want him to basically say, okay, I'm moving, but I'm turning around, so I need to do this little animation. So that's good. We want to be able to slow down, though. Right now, Mario doesn't have any friction, and that's not good. So let's go back into player controller and let's add friction. Okay, so we check if it's right or if we're pressing the left key. Otherwise, if we're not pressing either of these keys, we'll say this.acceleration.x equals 0. And then we'll say if this.velocity.x is greater than 0. So if we're going to the right, we can say this.velocity.x equals math.max 0, this.velocity.x minus slowdown force. So basically, we're going to say, hey, slow down until we hit 0 linearly using the slowdown force. Otherwise, if this.velocity.x is greater than or less than 0, we basically want to do this same thing, except we want to do the minimum of velocity.x 0 and plus. And then right here we can say if this.velocity.x equals 0, this.stateMachine.trigger stop running. So basically, if we have stopped, we will stop running. So now if we run this, we should have a sort of friction. And if we run to the right, he runs, and then once we stop running, we stop animating too, and then we can go move ourselves. And this is pretty good, right? This is an okay start to a player controller. This episode has gone on for way, way too long, though. Maybe not for you guys. Maybe it's only like 40 minutes, but it's been like an hour for me. So that's the magic of editing. But anyways, I feel like this is a pretty good start. In the next episode, what we're going to do is we're going to implement a ground checker. So basically, Mario will shoot a couple raycasts out to see if he's standing on ground. If he is, that will allow us to jump, and then we'll implement that variable length jump. And I don't know, maybe we'll start implementing like the blocks and stuff. We will see how far we get. In the last episode, what we got to was where we basically have Mario in here, and if we go and run around with him, we can sort of run, and he switches his animations based on what we're doing, which is all good. In this episode, what we're going to do is we're going to implement jumping and hopefully start on some enemy AI. So basically, we're going to implement it so that when we press spacebar or up, Mario jumps, and it's going to be a variable length jump. So in order to do this, the first thing we're going to have to do is create a way to check and see if Mario's on the ground. So let's go ahead and figure out how to do that. But before we do, very quickly, we have this annoying debug message, which was useful at the time, but we don't really need this. So let's just go into state machine. And we're going to get rid of this little warning because we don't really need that. And then we can go back into player controller. And we're going to be spending most of our time in here today. So let's go ahead, and the basic way we're going to check and see if Mario is on the ground is basically if we have like our player right here and we have a bunch of ground, we're just going to shoot a couple of raycasts from the left side of the player and the right side of the player, see if it hits the ground. If either one of them does, then we're going to return true. Otherwise, we're going to say we are not on the ground. So we're going to create a function, just call this public void check on ground. We're going to be reusing this quite a bit throughout other ones, so we may abstract this into its own utility type function, which we might or might not do in a little bit. So then we're going to have a vector 2f raycast begin, which is just a new vector 2f. This.gameObject.transform.position. So this is where the raycast is going to start, and we're going to say float inner player width. So this is going to be like a width of the player that's small enough to just barely reach the left side and the right side of the player. And I'm going to say that's this.player width times 0.6f, which is just a value I got based on messing around with things. Then we're going to say raycast begin.sub inner player width over 2.0f 0.0. So we're basically going to move the raycast start to the left side of the player, the bottom part of the left, or actually the center part of the left side of the player. And we'll visualize all this too. I'm going to do some drawing just so that we can see what's happening. And then what we're going to do is we're going to say float y value, or y val is the player state, which we don't have yet. So we'll create that in a minute, equals player state small. So if we're small, we have to raycast a smaller portion than if we're big. And we'll add in player state in just a second. That's going to be minus 0.14f. Otherwise, if we're big, it's going to be minus 0.24f, since we have to raycast a little bit farther down. Let's go ahead and create that player state very quickly, just so that we have that. So up here, our player is basically going to have like 3 states or 4 states. So we'll say enum player state is small. So when we have small Mario, big Mario, fire Mario, and invincible Mario. And I guess you could technically add in one for dead Mario, but that's just Boolean that we have that keeps track of that. I guess maybe it would be better in here, but I really don't care. And then we're going to go up to here, and we're just going to say, before all of these things, we'll say private player state equals player state dot small. So we'll start Mario off as small Mario. Now, once again, this y value is basically just how far do we have to shoot down to get the appropriate thing. And if we're big Mario, we have to shoot a little bit farther down than if we're small Mario. So then we'll say vector 2f raycast end. So where is the raycast endpoint? Equals a new vector 2f raycast begin dot add 0 y val, right? So we're just going down a certain amount of units, whatever our world units are. And then we'll say raycast info equals window dot get physics dot raycast, and we're going to give it our game object. Since we are requesting it, we're going to send it our game object so that if it hits us, we don't count that because we don't want to count hitting ourselves. Raycast begin, and then if we look at the parameters, raycast end is 0.2. And I guess we should call that begin end. It makes a little bit more sense, but it should be fine. Okay, so then we have our raycast info, and before we do anything with it, let's just go ahead and draw it so we can see exactly what's happening. So if we go ahead and say debug draw to add line 2D, and we're going to draw from raycast begin to raycast end, and we're going to give it a color of red just so that we know exactly which line it is. And then I'm just going to go ahead and import these. All right, so now if we go ahead and we just call check on ground inside of our update function, I'll do that right here because we're going to be doing it about here anyways. So I'll just say check on ground, and that should draw the raycast for us. So if we go ahead and run our game, you'll see we get this little red raycast, and you may or may not be able to see this very well because of YouTube compression, but you can see it's on the left of Mario. This is the raycast begin, this point up here, and this point down here is raycast end, and it's just barely touching the ground, which is how I wanted it. I want it to just barely hit the bottom of Mario so that we don't count him as on ground, since we have variable length jump if he's not actually on the ground. So this should do a good job, and you can see it's just barely over on his left foot, so we should get most of his body no matter what part of him is actually on the ground. Now we want to do the same thing for the right side of him, right? This will tell us if the left side of Mario is on the ground, but we also want to check the right side because he could be like standing on the edge of a block on the right side, and we need to be able to tell that too. So we'll say vector 2f raycast to begin equals a new vector 2f raycast begin dot add inner player width 0. So we're just going to move them over to the right, the width of the player, right? And we can say vector 2f raycast to end equals new vector 2f raycast begin dot add inner player width 0.0. And that shouldn't be raycast begin, that should be raycast end. Okay, there we go. Then we can get raycast info for that one as well. So we'll say info2 equals basically the same exact thing here, except we're going to be using raycast 2, and that should give us the information there as well. With both of those raycasts, we can tell if we're on the ground by saying on ground equals info.hit. So did we hit something? And info.hit object is not null, so we actually have a hit object. And info.hit object .get component ground.class does not equal null. So we've hit something, it has a hit object, and it also has a ground component. So either that or the same exact thing, except with info2, right? We want to check if the left side or the right side hit anything, and if either of them did, then that is a successful hit, and we are in fact on the ground. And I think right there, we should be good. Okay, so this should tell us whether Mario is on the ground or not. And then if we want to, we can just go ahead and draw that right line as well, just so that you guys can see where exactly that is coming from. So if I go ahead and add that in, and we run this one more time, you can see we've got two red lines on the right side and the left side of Mario respectively. Cool. So that should give us information about whether we're hitting anything. And we're not using this result right now, but it will tell us all the stuff that we're looking for, which is cool. Our physics engine is working and it's very simple to use, which is how I like it. So let's actually use this information and build a jump for Mario, right? Let's let him be able to create a variable length jump, or the player, I guess, in this case. So we'll say up here, if right after we check if we're on the ground, key listener dot is key pressed GLFW key space. So if they're pressing the space key and the jump time is greater than 0, so that means that they still, since it's a variable length jump, we want to check and see if they've exceeded the maximum amount of time they can hold the space key, which is what that jump time is for. We'll say, or we're on the ground, and I'm going to move this to a new line just so that we can see all this, and GLF or key listener that is key press GLFW key space. So if they're pressing space key and we have jump time left, or if they're on the ground and we have and they're pressing space key, or if the ground debounce is greater than 0, and key listener dot is key pressed GLFW key space, right? So if any of these things are true, then we basically want to check this, and we could probably simplify this a little bit more, right? Because we're checking if the key is pressed in all of these cases. So we could probably just change this to if space key is pressed, and then we can say jump time is greater than 0, or we're on the ground. So I'll remove that, or ground debounce is greater than 0. And that should be the equivalent logical expression, I believe. So we'll copy this, and then we should be able to just say or there. So, okay, there we go. So if they're pressing the space key and either the jump time is greater than 0, or they're on the ground, or ground debounce is greater than 0, then we want to go into this space here. And then what we'll say is if we are on the ground, or ground debounce is greater than 0, and jump time equals 0. So basically they've just pressed the jump key. They are on the ground, and we're basically just checking that. Okay, so they just press the jump key. We'll say play the sound. So we'll say get sound assets /sounds /jump small.ogg.play. So we'll play the jump sound since we just pressed the space key. Then we'll say jump time equals 28, which is a good value that I found for a variable length jump. And we'll say this .velocity.y equals jump impulse. Okay, and this is how we're going to simulate the impulse. We're basically just going to say instantly change the velocity, which is sort of what an impulse is. And this will make it so that we jump pretty fast at the beginning. And then we'll start using the acceleration again, which should mean we're going to use sort of a linear jump speed. You'll see. Okay, and we'll say else if jump time is greater than 0. So we still have some jump time left, and they are pressing the space key, right? We already know they're pressing the space key because we checked it up here. And then we'll say jump time minus, so every frame we take one away. This .velocity.y equals jump time over 2.2f, which was just a number I found that worked good, times jump boost, okay? So we're basically saying here, take the jump time. Initially, I had it as jump time times jump boost. So basically, we're just taking it as a factor of the jump time. So we start off at 28. And as time goes on, the player gets higher and higher, right? So the player starts off down here, we have the highest speed. Then the player gets up here and their speed is lower because we use 27 times whatever the jump boost is. And so it just linearly slows them down, but still gives them enough up force, which gives us sort of a quadratic type of curve, okay? If none of that makes sense, don't worry. It didn't really make sense to me either. I just sort of copied what they did in the original Mario clone, okay? And they'll say otherwise, if the jump time is not greater than 0 and they're not on the ground, then we'll just say this dot velocity dot y equals 0. So if they're still holding the jump key and they don't have anything left, we're just gonna ignore it and say, okay, 0 out their velocity, so they start falling again. And then right here, we'll say ground debounce equals 0. So that basically makes sure that if we just started pressing the jump key, right, if we're moving up, we don't want them to be able to press it again. So we're just setting this to 0 so that we don't count that anymore. Basically just resetting that value. Okay, so if they're pressing the space key, we've got that handled. Otherwise, if enemy bounce is greater than 0, we'll handle this a little bit later since we don't actually have enemies yet. So I'll pencil that out for now, and then we'll deal with that once we have a chance to. We'll say here though, else if we are not on the ground. So if we're not on the ground and we're not pressing the jump key, we'll say if this dot jump time is greater than 0. So if we're in the middle of a jump, then we'll just say this dot velocity dot y times equals 0.35f. So basically this just makes sure that, and then I'll say this dot jump time equals 0. If you release the space key a little bit early, I'm just going to slow down the vertical velocity and then set the jump time to 0 so that you start falling, but it's not like an immediate huge impulse when you start falling, right? This sort of slows it down gracefully. And I got all these values just by tweaking and messing with things until I got something that I liked. And we'll say here ground debounce minus equals dt. So basically, if we're not on the ground and we just want to subtract dt from the ground debounce. That way, if they still have some ground debounce left, they can still jump, right? So if they just ran off the edge of a block, this will start decrementing since we're not on the ground anymore. And then we can still jump even though we're not technically standing on ground until it goes below 0, then they can't. Then we'll say this dot acceleration dot y equals window dot get physics dot get gravity dot y times 0.7f, which you'll see is right here. So this will basically say, okay, only apply gravity if we're actually falling, right? We're not on the ground, so we're falling, so then we'll apply gravity. This way, we don't like hit the ground and we'll be able to glide over the ground a little bit easier. Otherwise, if none of this is true, so if we are on the ground, right? Because we basically just checked if they're pressing the space key and some other stuff. So that's the first one. Then we're saying otherwise if we're not on the ground. This is saying otherwise if we are on the ground. This is the only possible case we have left. Then we'll say this dot velocity dot y equals 0. This dot acceleration dot y equals 0. Ground debounce equals ground debounce times. Since we are on the ground, we'll keep resetting the ground debounce. That way, if they run off a block, then we start taking values away from that, but it's like they have 0.1 seconds left to do whatever they need to do. Okay, and then we get all this. We'll add in one more state machine trigger too. We'll say if we're not on the ground, then state machine dot trigger jump. So if we start falling, we just go into the jump state, or if we jump, we go into the jump state no matter what. If we're not on the ground, we go into jump state. Pretty self-explanatory. Otherwise, we'll say state machine dot trigger stop jumping. Okay. So jump or we're not jumping. There is no in between for that. So then we will go ahead and run this and see what happens. So if I hit space, you'll see I get this variable length jump. So I can jump small or I can jump high. And it's a little bit laggy, but you can see that I can control the length of the jump. And not only that, but it also gives me a nice smooth arc, right? It's fast at the bottom and then it slows down as I get towards the top. And then when we hit the top, we don't just start falling instantly. It's kind of like a graceful slowdown and then speed back up since we're using acceleration and everything, okay? We can check out if the other feature is working too. So if I drop one of these guys in, and we should actually be able to jump 4 blocks up. So if I put this, yeah, I believe this is the highest we should be able to jump, right? Yeah, that looks about right. Maybe we can jump 1 more block. I'll try that. Oh, and you'll notice there was a problem there. If we hit the bottom of a block, we're still going up. So I'll put that up there, see if we can jump. Okay, so it looks like we can jump up to this block. I'm not sure if that's how I have it in the original, but you'll notice some problems, right? For instance, if I hit that block, I kind of keep my forward velocity. It's not canceling out my velocity. And you'll see I got stuck there for a second.
If I hit the top of the block, you'll see I kind of float there for a second. That's something we need to stop too. So these are a couple of problems that we'll fix now. Let's go ahead and actually do that. So how can we check if we're hitting the bottom of the block or the top of the block or any of that stuff? We can use our collision events, right? I'm going to comment those out for now because we don't really need those anymore. So we'll say override public void begin collision, which takes in a game object, colliding object, takes in a contact, and it takes in a vector2f contact normal. Okay. So first of all, if we're dead, we don't care. We'll return. We don't need to do anything if we're dead. We don't really care about anything. So I'm just going to put that in there so we have it. And we'll say if colliding object.get component ground.class does not equal null. So if we hit something that is of the type ground, we're going to check which direction we hit it. We'll say if math.absolute value of x or contact normal dot x is greater than 0.8f. So what am I doing here? I'm saying, did we hit it horizontally, right? If it's greater than 0.8f, I can say with a pretty high certainty that we hit it horizontally because we're trying to correct it left and right, not up and down. Then we can say this dot velocity dot x equals 0. So this should take care of us hitting it to the left and right, right? If I run into this block, you'll see I lost all my forward velocity. I just sort of fell. I didn't keep going to the left and to the right, and we still got a bug there, which I'll see if we can fix. But yeah, it just stops us in our track, and we can do this a little bit more too, right? If I put a block here and then I go and run into it, it instantly stops me. I can start speeding up immediately again. If I take this away and we run into this block again, you'll see that it's hard for me to turn around. Okay, so that's why this is important. Now we'll say else if contact normal dot y is greater than 0.8f. So what are we checking here? We're saying otherwise if we're hitting the top of Mario. So in other words, if we're hitting the bottom of a block with Mario's head, right? That's why we're not taking the absolute value here. Then we'll say this dot velocity dot y equals 0. This dot acceleration dot y equals 0. This dot jump time equals 0. So we'll basically zero out all of our vertical velocity so that we just fall back down. So now if I hit this, I just fall back down. Even if I hold space, I can't keep going up because we've hit the bottom of the block. So that's another good thing that we needed, and it just sort of works, which is nice. Let's also go ahead and real quickly, because this is bothering me, when we hit the bottom of this block, it should bob up and down, right? Because that's how Mario works. So let's go ahead and implement that really quickly. So let's go into breakable brick, which I thought we created. Maybe we didn't. I said we would do that in this episode, which we will. So let's go into level editor scene initializer where we have this right here. So we'll say object.add component new breakable brick, which is just a brick that we can break, right? Self-explanatory, hopefully. And then we'll say this is breakable brick, and we're gonna say that this extends component. And we should be able to just say at override. Actually, okay, yeah, so I did this a little bit differently. Since we have a couple different kinds of blocks that can be hit from the bottom, like a coin block or a breakable brick, I had these inherit from a common ancestor, which I don't usually do, but it seemed appropriate in this case. So I created another component, and we'll call this block, okay? And this one is going to have an abstract method that we can use. This will expend component, and this will sort of be the base for any sort of block that moves up and down when Mario hits it, or can break or do whatever, right? So we'll say private transient boolean bop going up, okay? So I literally just called it bop because that's what makes sense to me. Private transient boolean do bop animation, right? So are we going to do the animation? That's false initially because he hasn't hit it yet. We'll say private transient vector 2f bop start. So where did we start this? And we'll just initialize that to nothing. Private transient vector 2f, we'll say top bop location. So where do we stop going up? And then private transient boolean active equals true. So can we still go up and down, or can we no longer go up and down? And then lastly, I added in a variable that can be tweaked if you want to, called bop speed. And I think I just set this to 0.4 f, and that should be good. Then we'll say at override public void start. So on start, we'll get the start position in the top bop location. So we'll say this dot bop start. Oh, and I called that bob. That should be bop.
equals new vector 2f, this.gameObject.transform.position, this.top bop location equals new vector 2f bop start dot add 0.0f 0.02f, which was a good distance for me. You can tweak all these values if you want. Next, we're going to override the update method. So say public void update float delta time. We'll say if do bop animation. So if we want to do the animation, we want to go up and then we want to go down, right? When Mario hits the block, it just goes up, then it goes down. That's all we got to do. We'll say if bop going up. So if we're going up, if this.gameObject.transform.position.y is less than the top bop location.y, then we're going to keep going up. We'll say this.gameObject.transform.position.y plus equals bop speed times dt. Otherwise, bop going up equals false, right? So if we hit the top of the location, then we'll start going down. And then if we're not going up, then we must be going down, right? So then we'll say if this.gameObject.transform.position.y is greater than bop start y, so we still need to go y, or still need to go down. We'll say this.gameObject.transform.position.y minus equals bop speed times dt. And then we'll say else this.gameObject.transform.position.y equals this.bop start.y. So this is kind of important. It's something I've just picked up from doing games. If you ever have something that's supposed to result in ending in its initial location, you should always just reset the value, because floating point errors will make us that slightly off. And if it keeps getting slightly off every time, then your game object will eventually veer off quite a bit. So we just reset the value here if we're done doing the animation. We'll say bop going up equals true, so we reset it so that it can do it again if it needs to. We'll say do bop animation equals false, so we say stop doing the animation. And then down here, we'll say at override, public void begin collision, game object obj, contact, vector 2f, contact normal, so just the normal collision stuff, import this. Say player controller equals object.getComponent, player controller.class. And then we'll say if we're active and player controller is not null, so we actually got a player controller on that, and the contact normal.y is less than negative 0.8f. So that should be contact normal. We're checking, first of all, can we do the bop animation? If we can, then we will. Did the player hit us? If a player hit us, then we need to do the animation, but only if the player hit the bottom of our block, which we can check by just seeing if this is less than a certain threshold, which minus 0.8f was good for me. We'll say do bop animation is true if this is all true. And we'll say asset pool dot get sound assets slash sounds slash bump dot ogg dot play. And then we will say player hit, and we'll give it the player controller. Then we're going to give this an abstract void player hit, and this will take in a player controller, the player controller, right? So this is an abstract method that we can call. What's wrong here? This is a non-abstract class. No, this is an abstract class. So let's make this abstract. You can't instantiate this. We just call this method, which gets implemented by whoever inherits from us. And then we'll have this public void set inactive function, which basically just sets us to not active. So this would be for like question blocks where you can hit it once, but you can't keep hitting it after that. So perfect for those. And then we can go into here, instead of this inheriting from component, we'll inherit from block, and then we will implement this player hit method. And then we'll basically just say up here, if player controller.is small, which we'll implement in just a second, asset pool dot get sound assets slash sounds slash bump dot ogg dot play. So if they're small, we'll just play the bump sound, which I don't think we even have to do, because yeah, we play it in here. So if it's small, we don't really have to do anything. So I guess we could just change this to if it's not small, and say we basically want to break it in that case. So we'll say get play sound assets slash sounds slash break block dot ogg dot play. And then we'll say game object dot destroy. So we'll destroy our game object and we will play the sound. And I guess we maybe don't want to play the sound in here because it'll play regardless. We'll think about that. You can change that right now if you want to, because that's probably the better thing to do, where we don't play it inside the parent class and only subclasses can play it if they want to, because that's probably the best thing to do. Inside player controller though, let's just say public boolean is small. We'll return this dot player state equals player state dot small. All right. And then if we play this, we should be able to hit the bottom of this block. If I can hit it. Okay, and it's not doing anything. Why not? Because we just changed the prefab, but we haven't actually updated this. So now if we go ahead and put that in again, we should be good. There we go. Okay. It's vibrating. Looks like I probably messed something up because this isn't going quite right. So let's go ahead and look through this again. Oh, and it looks like I just placed this else clause in the wrong block. So that should be right down there. And if we go ahead and do this one more time, let's see if this works now. So if we go ahead and hit this, still not quite right. Let's see what else we got wrong. And you know what I think it is? I think it's if we go into rigid body, this one, there was one thing that I implemented that I completely forgot about. So if we scroll up to the top, we basically say we're going to set the position regardless of whether we have a dynamic body or a static body according to Box2D's physics, right? Where actually what we want to do is we want to say if this dot body type is body type dot dynamic, or this dot body type is body type dot kinematic. If we have either of those, then we want to do this where we sort of tell our game object, hey, just align yourself with the physics engine. We want to use whatever the physics engine says we should use. And actually what we want to do in this case too is we'll even say vec2 vel equals raw body dot get linear velocity. And we'll even say this dot velocity dot set vel dot x vel dot y. That way we set ourselves to the physics velocity too, and we could do the same thing for all our values. That could be changing while physics is running. Otherwise, if we have this dot body dot type equals body type dot static, which means the body should never be moving, then we want to say this dot raw body dot set transform to a new vec2, this dot game object dot transform dot position dot x, this dot game object dot transform dot position dot y, comma angle 0.0f, which we could technically use the game object's angle to, which is probably a better value anyway. So I'll change that to this dot game object dot transform dot rotation. All right, and that is a much better value to set. So we basically say, hey, physics engine, set this to what I want to set it to. So if we implement these changes and run this one more time, then we should see, yeah, okay, so the block goes up, then it goes down, okay? And it does it the correct way. What was happening before was basically we were trying to set it up, but then the physics engine was saying, no, this block is actually down here. And then it was just sort of jittering because it was trying to go back and forth between two positions because the physics engine and my engine were fighting based on what position it should be. So we basically tell the physics engine, hey, if we are using a static body, we control the position. Otherwise, you control the position of the object, and we'll just sort of let you do that. Okay, so that's why that worked. I guess since we're going along this route too, instead of doing enemy AI today, we'll just do the question block, right? So one of the blocks we have in Mario is a question block, which can put out a power up or a coin, depending on whatever you want. So we'll actually have this, right? We already have it so that we can generate it, and we have the animation, which I called run. Let's just change that to flicker, since that is what the question block is actually doing. So I'll just change all of that. Should be good there. And then we actually want to add one more animation state too. We'll say animation state inactive equals new animation state. So when the button is done, and then this is just going to be, first of all, the title is inactive, and then we can say inactive.add frame player sprites, which is actually the item sprites in this case, get sprite 3 0.1f, this, or inactive dot set loop false. So we don't want this to be a looping animation. And then we can go ahead and just say right here we have the state machine. We'll add the state to inactive. We can say state machine dot add state. So we'll add a transfer here, flicker dot title. So we'll go from flicker to inactive on set inactive. Okay, so that's the trigger, and that should all work out properly. Okay, and then we'll go ahead and we'll also say question block to add component new question block, which we will create in just a second. And then we'll go ahead and say rigid body RB equals a new rigid body, RB.set body type to body type dot static. Then we'll say question block dot add component RB. Then we will say box 2D collider, B2D equals new box 2D collider, B2D dot set half size to new vector 2f, 0.205f, 0.25f. So we set the size of those. And then we'll say question block dot add component B2D. And then we'll also say question block dot add component new ground, because it can also act as a ground component. And then we just return the question block as normal. Let's go ahead. We'll create a new component in here. We'll call this question block. And now we can use that fancy parent component we just created, right? We can just say this extends the block class. And if you were using a functional language or something, you can accomplish this exact same thing using functions, okay? I don't think inheritance is special at all in this way. I would use a completely different technique in C++, for instance, than inheritance, because I think it's overkill for this, honestly. Okay, but anyways, with that aside, let's go ahead and implement this. So we're going to go ahead and we're going to say private enum block type, and this is going to have a coin, so we can have a coin block, a power up, or invincibility, which I don't think I ever had an invincibility, but it's there, and I'll leave that up to you guys to implement. So we'll say public block type, block type equals block type dot coin. So we'll just have these as coin blocks initially. And then let's go ahead, we'll implement this method. And I'm just gonna put this below all that stuff. So we'll have player hit, and we'll say switch on the block type. If we have a coin block, then we'll say do coin player controller break. Otherwise, if we have a power up, we'll say do power up player controller break. Otherwise, if we have invincibility, do invincibility player controller break. And then after we do whatever we do, we just want to say state machine equals GameObject.getComponent state machine.class, and we'll say if state machine does not equal null, then we'll just trigger set inactive, and then we'll say this dot set inactive. Okay, so we trigger it, and then we also set it in the block type so that we can't bop it up and down anymore, because we are extending from the block class, right? Okay, then we just need these functions. So I think if I hit Alt Enter, we can say create method. Just hit escape, that should be fine. I'll do the same thing for this one. Hit Alt Enter, hit create method, that should be fine. Same thing here, create method, we should be good. Okay, cool. So then if we go ahead and go into do the coin, so we want to do coin, we'll say game object coin equals prefabs dot generate coin, or block coin, since there's coins and then there's coins that come from blocks, and we'll go ahead and implement this as well in just a minute. For now, it's not there. We'll say coin.transform.position.set, this .gameObject.transform.position. So it basically starts from inside the block. Well, not quite inside. We'll say position.y plus equals 0.25f. So we'll have it start to like one block above this block, and then we get the scene, and we say add game object to scene coin. Okay, so once we actually get this implemented, it should all work great. For now though, if we just go ahead and add a question block, we should be able to hit it and it should go to the inactive state. So if I go prefabs, add in a question block here, we click onto it, and you should be able to see we have a coin block here, and we can change that in the future and now if you want to. And if we hit it, it turns into that block, and we can no longer bump it. We can bump this one multiple times though. Okay, so that's sort of the first step. Now let's go ahead and implement this coin block real quickly. So we'll uncomment all that, and then we'll go into prefabs, and then we'll go ahead and we'll say public static void game object generate block coin, and we need the items. I'm just going to copy this because we're going to have a lot of the same stuff. So go ahead and copy that, and then I'm actually going to call this items because that is what this is. And this is a coin. This is not a question block, and we'll say this is going to use items dot get sprite 7. We want it to be the same size. We'll have an animation state coin flip.
and we will call this coin flip. So we'll change the title up here as well. Then we just want to add items here. We want to add in 7, 8, and 9. We do want this to loop. We don't want a second animation, so we can remove that. We can remove that. Then we'll just add the flip here, add it here. We do not need any triggers since we just have one thing. And then we can go ahead and say add it to the coin. And I will do all this stuff as well. And we don't even need a hitbox or anything on this since it does not really do any of that stuff, right? So we'll just say coin.add component new block coin, which we'll add in just a second. Oh, and I said public static void game object. Remove the void there if you copied me. Okay, that should just be public static game object. All right. And then let's go into here. We will add a new component block coin. We'll say that this extends component. All right, and then we'll say private vector 2f top y private float coin speed equals 1.4f. Once again, these are just values that I found that were good. And then we'll say override public void start. Then we'll say top y equals new vector 2f this dot game object dot transform dot position dot y dot add 0.5f. So this is how far I want it to fly up whenever you hit it. And we'll say asset pool dot get sound assets slash sounds slash coin dot ogg dot play. So basically whenever it gets instantiated into the game world, it'll play the coin sound. This is why it's different than a regular coin, because you wouldn't want it playing coin sounds every time you just drop a regular coin in the world. Then we'll say override public void update float delta time. We'll say if this dot game object dot transform dot position dot y is less than top y dot y, and this is where it's different too than a regular coin. We don't have to wonder if it's doing the animation, because as soon as it gets instantiated, we know it's going to do the flying up animation. So we'll say this dot game object dot transform dot position dot y plus equals dt times coin speed, and we'll say this dot game object dot transform dot scale dot x minus equals 0.5f dt times dt modulus negative 1.0f. So this is basically going to make it so that looks like the coin is flipping as it goes up, as we just change its scale. And we'll say otherwise, if we've reached the top, then we'll just destroy this game object, and you could count it towards the player and all that stuff too if you wanted to. Now if we play this, we should be able to say generate block coin, and then we should be able to play this. And if we go ahead and hit this, you'll notice we get the coin, right? We hit it and we get a little coin, and we can't hit it again because it won't let us, but we could duplicate this. Well, I guess we can't duplicate. Something went wrong there. I think it did duplicate. It's just not showing up, right? Yeah, if we play it, we see it there. We can fix that pretty easily too, and we probably will in just a minute. So you see we can get coins, right? That's pretty cool. We'll add the power up and everything in the next episode because this one has been going on for too long. But I hope you guys enjoyed this. If you did, please hit like and subscribe. And in the next episode, we'll be adding power-ups and enemies, all right? So basically, you can hit this, pop out a mushroom or a flower, and we will have Goombas, not quite the turtles yet. I think we should be good just implementing those two features in the next episode. I'll see you guys then. Thanks for watching. In the last episode, we got to the point where we now have coins popping up out of our power-up blocks, and we can bop our blocks so they go up and down, right? So if I were to just run as Mario, we can bump those blocks and we sort of get some coins popping out of there. In this episode, what we're going to do is, first of all, there's a bug where, say I duplicate this, you don't see it until we refresh, and that's because we have an issue with our batches. And it looks like it duplicated that twice, so that's another thing we'll have to fix. But yeah, so we basically have a problem with our batches where we don't get to see those updates. So let's fix that real quickly. It's pretty easy. If we just go into render batch, the problem that we are facing is basically whenever a sprite is dirty because it's had a texture change, we're not checking for that. So the way we can check for that is we can literally just say, first of all, if the sprite is dirty, that means something about the sprite has changed. And then we can say if we don't have the texture, so in other words, the texture has changed on this sprite and it doesn't actually appear in this batch, we need to move this sprite to a different batch. How do we do that? Well, it's pretty simple. First of all, though, let's just go ahead and we'll say do that otherwise, because we don't care if it has the same texture, then we can just continue. But if we need to move this to a different sprite batch, we can do that pretty simply just by saying this.render.destroy game object, and we'll give it the sprites game object. So we're essentially going to remove it from this batch by telling the render to destroy it. It's not really going to destroy it from the entire world, just the render, which is what we want. And we can say this.render.add sprite.game object. All right, so we just let the render take care of this for us. I mean, it's already built to do that, so let's take advantage of it. Now, if we, first of all, delete that. If I duplicate, you'll see we almost get it, but now it's black. And why is it black? Okay, and that took me way longer than it should have. I actually had this as a bug in my final thing too, so I couldn't figure out what was wrong. But what's happening there is basically when we duplicate objects, remember how if we're placing objects, we have to refresh the state machine's textures? Well, we have to do the same thing when we're duplicating those objects too. So if you just go into key controls and then go under where we do the duplication logic, if you just check and see if this object has a state machine, refresh those textures, and that should fix the problem. We also want to check it if we have multiple game objects, so we should copy this, and then we'll just go ahead and place it in here, and we'll do this with the copy. I don't think it's necessary when we're, well, yeah, it's probably necessary in there too. So now if we duplicate, we're fine. If we duplicate multiple objects, I think I duplicated those. Let's see. Duplicate multiple. Yeah, I think I just made a bunch of copies. Delete, delete, delete. Okay, yeah, now we're good. Cool. It's working good though, right? So we fixed that. We just need to make sure that we were duplicating those, and now everything is working good. One other thing I'm curious about real quick too. These are out of sync right now, but if we hit play, yeah, they're still out of sync. We might want to fix that in the future. For now, I really don't care. Anyways, that's good. Now we want to get power-ups working, right? So if we hit that block, we should get a power-up. So let's go into question block, and let's go ahead and implement that logic. Shouldn't be too difficult. I believe, yeah, so we've already gotten the do coin, do power-up, do invincibility, so that's all good. Now let's just go to the do power-up. I'm not going to do invincibility. I'll leave that for you guys to do as an exercise after the series is done. Basically, we can just check and see if the player controller is small. If it is, we want it to be big, so we'll say spawn a mushroom. Otherwise, I guess we could just say else, because if it's, technically we should check if it's big, so is big, and we can go ahead and implement that real quick, because if it's not small, it could be invincible, or it could be fire, or it could be big. We don't know, so we'll just say is big. Actually, I guess this doesn't matter. Okay, so let's go back into question block. We don't care if it's big or if it's fire or if it's invincible, because basically, no matter what size the player is, we want to spawn a flower if they're not small, right? If they're small, we spawn a mushroom. Otherwise, we just spawn a flower. So we'll go ahead and write that real quickly. And these functions will be very similar to the do coin, except we will just be spawning mushrooms and flowers instead. So we'll say spawn mushroom, and we'll have private void spawn flower. And for spawning a mushroom, what do? Well, we want to generate a mushroom first of all. So we'll say prefabs.generate mushroom, which we don't have, but we will. It's pretty simple. We'll say mushroom.transform.position.set to this guy's position. All right, same thing we did with the coin. And then we're going to go ahead and also say mushroom.transform.position.y plus equals 0.25f. So then we'll just put it on top of the block, which is where we want it to spawn. And then we can just add it to the scene. So we'll say add game object to scene, mushroom. I'm going to copy this because it's literally going to be the same thing for the flower, except this is going to be a flower, and we're going to be generating a flower. All right, and we'll implement all those functions in just a second. I'm going to comment this out for now, just because we're going to be doing that after we make sure the mushroom is working properly. So let's go ahead into prefabs, and we want to create a generate mushroom function. So let's go ahead and copy generate block coin, because this is going to be pretty similar. Paste that down there. We'll call this generate mushroom. All right, and we are going to be using
the items.png, and we're just going to get a mushroom game object, right? This is going to be game object 10, or I mean sprite 10 inside of this sprite sheet. And the mushroom actually does not have any animation, so we can get rid of that. That makes our lives a little bit easier. It's also not a block coin, so we don't care about that. And then we're going to be returning a mushroom, of course, but we do need to add some physics to this guy because he's going to be doing a little bit more than our other dudes. So we'll say rigid body 2D, RB equals a new rigid body 2D. Give him rigid body. We'll set the body type to a dynamic body. We're going to do sort of the same thing that we did with Mario, where he's affected by gravity, but we kind of control gravity and all that stuff. And we'll say set fixed rotation to true. And technically this stuff doesn't matter since we're going to be controlling all this, but we'll set it anyways. And then we'll say mushroom.add component RB. And then we also want to add a collider, circle collider. So we'll say circle collider equals a new circle collider. And then we'll say circle collider dot set radius to 0.14f, which was what I found to be good. And then we will also add that. So to the mushroom, we'll add the component circle collider. And then we're also going to add a component, which is a new mushroom. And that will basically be the mushroom AI. I guess we should call that mushroom AI. And then he will have that attached to him. What does that AI look like? Well, let's go ahead and create it. So we'll just create a new class in here, call it mushroom AI. We'll say this extends component. Make sure you import that from the right package, which we actually don't need to import it. Let's go ahead and override public, if I can spell right, override public void update float delta time. And we're also going to need to override public void start. And we're going to need a few variables. We'll say private transient boolean going right equals true. So we're going to have them all going right initially, just because that's how it works in the original game, I believe. And then you can change that. So I think we may be changing it in certain scenarios. I'm not sure. I don't know. We'll see. But then we'll have private transient rigid body 2D RB. So we'll just get a hold of the rigid body. Transient vector 2F speed, which we're going to set to 1, 0. Those were the best values that I found. Private transient float max speed equals 0.8f. So that's like its terminal velocity. So this speed will basically just automatically put him to the max speed almost. So it's like he has no acceleration time, which is what we want. And then we'll have private transient hit player equals false, which this is a Boolean, and it'll just help us keep track of whether or not we've already been consumed, because there is a chance that he's on screen for a couple frames and we just want to make sure that we don't enable collisions. So this is going to help us keep track of that. So anyways, when we start, we're going to say this .rb equals gameObject.getComponent rigidbody.class, and we're going to play the sound because he should only be appearing whenever he gets spawned in. So we'll say play the sound power up appears.ogg.play. And we're going to be making use of the pre-solve function for this guy. So that's cool. We'll get to learn some new stuff. But we'll basically say if we're going right and the math.absolute value of rb.getVelocity.x is less than max speed. So if we're going right and we're not at the terminal velocity yet, we'll say rb.addVelocity speed. Okay, so I guess we actually do let this guy be controlled completely by physics. That's what it looks like I did. So he is controlled by the physics engine, and we just sort of apply some velocity to him, which is cool. We'll say otherwise if we're not going right, and math.absolute of rb.getVelocity.x is less than the terminal velocity. Then we'll say rb.addVelocity new vector 2f negative speed.x and speed.y, which speed.y is just 0, so it's not really going to do anything. But yeah, that should be good. And if we go ahead and test this out real quickly. So we're going to go ahead and make that question block a power up. And if we hit play, we should spawn a mushroom. Or we can crash. I mean, that's always fun too. So if we look at that error, world.createBody right here, we got an assertion error. I bet you we tried to create something while we were locked. Okay, physics 2D create body. If we look in here, yeah. So if we look in here, I'm guessing this is the assertion we hit, which is assert this is not locked. It's not telling us exactly. It's breaking here, but I'm guessing it's hitting this because it said it was an assertion error. Okay, so how do we deal with this? Well, what's happening? Okay, let's think about this for a second. If we look at our question block, we basically are spawning this mushroom. Well, what is spawning this mushroom doing? He's creating a new game object at runtime, and he's adding it to the physics engine, okay? And the physics engine doesn't like that, because if we try and add stuff to the physics engine while we're in the middle of a physics update, it screws things up. So the way we can mitigate this is if we just go into scene, we can just create a queue of game objects that need to be added, right? So up here, we'll have another private list of game objects. And this will be called our pending objects, okay? So these are the objects we want to add this frame, but we're going to wait because we don't want to add it in the middle of a frame because that's icky and causes problems. So we'll say pending objects is a new array list right here. And then when we add a game object to the scene, we basically do all this junk. Well, instead of doing that, let's say if we're running, so we're in the middle of gameplay, we'll just say pending objects to add go. Okay, cool. So that's going to simplify things a little bit more. I'm going to copy that just so I have it in my hotbar or my paste, my clipboard, whatever it's called. Then let's go down to editor update and update because we are going to need to modify both of these. So right here, we loop through all of the game objects. We update them, which is all good. Then we'll loop through all of our pending objects. And we'll say paste that stuff. We'll add it to the game objects. We'll start the game object. We'll add it to the render. We'll add it to the physics. And then we can say pending objects.clear. Cool. So that should take care of this, I believe. So basically, we just wait till the end of the frame. We finish updating everything. And then once everything is done, we add it to the physics in the render. That way we don't end up doing gross stuff. So let's see if that works now. If we run and we hit this guy. Yeah, cool. So now we get a mushroom. He is not moving, but we can sort of knock him around. Oh, and he started moving there. Let's see. I probably forgot to add something, which is why he's doing this. But it's pretty cool. And you can hear it plays the sounds and everything. I don't know how loud it is for you guys, but yeah. We've got our little mushroom buddy. And I think I just found the bug. So basically, if you go into rigid body 2D, I was stupid. And where we have add velocity, we're just adding nothing to the velocity. We should be adding the force that we want to add to that velocity. So if we go back into there and we hit play, and the reason the mushroom was going once we hit him was just because he had a velocity, so he wasn't stopping. There we go. So he starts going to the right, and then if he were to hit something, what would he do? Well, I'm guessing he wouldn't do much. Let's delete that, and then we'll add a new guy right there. So if we go ahead and press play, if he hits me, he just keeps trying to go right. We don't want that. How do we fix that? Well, we use our pre-solve method, and we're doing this in pre-solve for a very specific reason. So let's go ahead and we'll say pre-solve, which takes in a game object, obj, a contact, a vector 2f, the contact normal. So we get all of this information, who hit us, how did they hit us, right? That's the important stuff. Making him switch directions is pretty easy. We just say if math.absolute value of contact normal dot y is less than 0.1f. So if the contact normal was more horizontal than it was vertical, we'll just say going right equals contact normal dot x. Contact normal dot x is less than 0. So if it's less than 0, which means that the contact normal was negative, which means that we got hit on the left side, going right is now true. So we are now going right. Otherwise, we are now going left. So this will be false. What happens if we just do this though? So if we go and we run this, he should switch directions. Sweet. And then what happens when he hits us? Well, he just switches directions again. But also notice one thing. When he hits us, he pushes us. That is not what we want. We want him to stop colliding with us. He basically just does not intercept with us. He doesn't care. There are two ways you can accomplish this. One way is by using collision layers, right? We could have a collision layer, which is players and power-ups. Player does not actually collide with power-ups. So you basically have player, power-ups do not collide, but player power-ups collide with the ground and everything else. That's possible in Box 2D, but there is a simpler way, which is kind of hacky, but it's the way I went with because it just makes sense for this. So we could say player controller is the object.get component player controller dot class. So did we hit the player. So did the mushroom hit the player? So if the player controller is not null, we clearly hit the player, and we can do something called contact.setEnabled false. Since we are in pre-solve, setting the contact to false basically means don't solve this contact, which should mean that the mushroom doesn't collide with us. Now let's see if that actually works, because I was having problems with it in production, but we'll see. So theoretically, the mushroom should go through us. He doesn't go through us, but you'll see we don't go back, right? He doesn't apply any force to us, which I guess that is just as good, right? If we just keep going, we can clip through the mushroom now. So that's pretty cool. Yeah. And actually this makes more sense, right? Why are we clipping through the mushroom? Why is he not applying any force? Well, it's because of this line right here. We basically check. So we're still getting the contact normal and everything, but then we set this to false. If we just do this afterwards and then we just return. So if we hit the player, we just sort of exit early, then the mushroom should go right through us, which is what we want. And this is another important concept. There we go. You see, he went right through us, didn't do anything. This is an important concept because this is how you would do like one-way doors and stuff like that, one-way traps, one-way platforms, whatever, where you could jump through one side but not the other side. This is how you would do it in Box2D. So take this concept, explore it more, do some cool stuff with your games, and show me in the Discord, because that would be awesome. Anyways, let's go ahead and power up the player if we actually hit him. So if we didn't hit the player, which means this is the first time we've hit him, this is that we don't accidentally power up multiple times. So he like goes mushroom, then he goes to Fire Mario, then invincible, whatever. We're just going to call this once. So we'll say player controller.powerup, which we don't have yet, but we'll add. And we'll say this.gameObject.destroy. So we destroy the mushroom, and then we'll say we hit the player now. This way, the next time this function is called, if it's called multiple times, we don't end up powering the player up twice. Okay, let's go into the player controller and create a power up method. We'll put it right above the collision. So we'll say public void power up. And it's nice to do this here and just sort of abstract it, because we don't want to care about like, is he Big Mario going to Fire Mario? We'll just sort of let the player deal with that, right? So we can go into here and we can say if player state is player state.small. Right there. What do we want to do? We want to be Big Mario. So we'll say player state equals player state.big. We'll say asset pool.get sound, assets/sounds/power up.ogg.play. So we play the power up sound. And this is actually going to play, well, no, it's not going to play regardless. It only plays if we actually power up. So I'll leave it like this. For instance, you could get fire when you're already fire, and that doesn't actually power you up. Then we'll say gameObject.transform.scale.y equals 0.42f. Mario actually gets bigger, so we want to change his scale to reflect that. Then we also need to reset the pillbox collider, because the pillbox collider bounds are going to change. So we'll get that component. And we'll say if PB does not equal null. Then we want to say jump boost times equals big jump boost factor. So we let him jump a little bit more forcefully. And then we say walk speed. That was, and we're going to multiply this also. The reason I did this initially was just because I was using Box2D for actual physics. And when you change the size of a collider, it actually changes the way that forces work, because the mass gets spread out in a different way. So physicsy stuff basically makes the forces act differently, and this was to accommodate for that. We shouldn't have to worry about it with the way we're doing it now, but it's good to have it there anyways. Then we'll have set height to 0.63f. So we reset the height of the pillbox collider to reflect his new height, which should be good. What if he's not small? What if he is? Player state equals player state dot big Mario. Well, if he's big, we want to set him to fire. So say set the state to player state dot fire. And then we want to say asset pool dot get sound, this thing. Exactly the same thing. And then last thing we want to do, state machine dot trigger power up. And we don't have to do that differently for small or big Mario, since we already set it up to work appropriately. Cool. So this should help us for powering up big or small. If we run this, we should hit that, and we power up to big Mario. Cool. And that's still a little bit buggy. I'll have to look into that, see what's going wrong. But yeah, we got big Mario. Sweet. Now let's make it so that we hit this one. Should pop out a mushroom. And if we duplicate that, since this guy is also a power up, he should hit out a flower. That is if we're big Mario. He does nothing right now. Why? Well, we didn't implement that. So if we go back into here, we have this spawn flower method. Let's go ahead and actually implement this. We'll go into prefabs. Let's go all the way down. And this one's going to be way easier than the mushroom because we don't have to worry about any sort of physicsy stuff. I mean, we do a little bit, but it's way easier, right? We'll just say generate flower. This is now a flower. His index is 20. Nice. And then we want to give him a rigid body, except he's static. Why? Because the flower doesn't move. It just sort of sits there. We don't care about gravity or anything. We're just going to place it in the correct position, and that's that. And then we're going to add the rigid body to the flower. We are also going to give him a circle collider with 0.14f. And then we're going to say add the circle collider and add flower, new flower. I'm not going to say flower AI because it doesn't have any AI. It's just a flower. So then if we go back into, or actually we don't need to go into anything. We just need to add a flower component. So if we go into here, say this extends component, and this one is fairly straightforward. We'll just get a reference to the rigid body. So we'll say at override public void start this.rb equals gameObject.getComponent rigid body.class. Nicely done. We also want to make sure to play the power up sound. So we'll say get sound assets /sound /power up appears .ogg.play. And then we're going to say this.rb.set. Ooh, a new thing is sensor to true. Well, I guess this is just going to set it as a sensor. What is a sensor? We talked about this a little bit. A sensor is just something that doesn't actually collide with anything. So we can do this with the flower since it doesn't collide with enemies or anything like that. And this means we can just run right through it. So if we were to actually run this real quickly, we can get the mushroom. Well, we got 2 mushrooms there. That's also a good test, right? We got 2 mushrooms. Why? Because we were a little Mario when we hit both of those blocks. So if we get that and we spawn in a flower, we can run through it and it doesn't stop us, doesn't apply any physics. That is what a sensor is. Those are useful if you just want to trigger or something. Use a sensor. Anyways, we actually want our flower to do something when we hit it though. So we'll say public void begin collision. This takes in the game object, the object colliding, takes into contact, the contact, and it takes into vector2f, the contact normal. Let's go ahead and import all this stuff. Import that, import that, import that. And we can say player controller equals gameObject.get, or not gameObject, I'm sorry, obj.getComponent, player controller.class. If the player hit the flower, then we want to power the player up. We'll say contact.set enabled to false. Technically, we don't need to do this. This is a sensor. I'm not sure why I did that, so we could just leave that out. And we'll say player controller dot power up. We will say this dot game object dot destroy. Okay, cool. So this immediately destroys the game object. We might have problems with this. I don't think we should because I think we queue that up, so it should be destroyed at the end of the frame. So if we go and we hit that first one, we power up, we hit this one, and we power up to Fire Mario. It's all working. That is good news. I like it when things work. Unlike the beginning of this video when I messed stuff up. Okay, I'm going to leave it here for now. In the next episode, what we're going to be doing is enemy AI. So we'll probably implement the Goombas and the turtles, get those in the game so that we can use them. And then we're going to get pipes done, and then we're going to get fireballs working. And we need to get the flag so that you slide down the flagpole at the end of the level. And then that should be good. Like, that's pretty much Mario. I hope you guys can begin to see how this is able to build a pretty good game, and you can sort of use our engine now, not have to worry about too much stuff, and it all just sort of works. If you were to build your own game, it would follow something similar like this. One question for those of you who are still with me. So OBS does not capture the mouse cursor very well. Like if I go into here, you'll notice that you can see the mouse cursor over here, but when I move it over text, it doesn't capture it for some reason. So do you think it's better for me to have this highlighted thing and then capture it? Or I could alternatively turn on this magnifier, which captures it everywhere. The only problem is the magnifier messes up my mouse cursor, like when I'm doing certain actions, which is annoying. So let me know if you think the yellow cursor is perfectly fine for all this stuff, or if you would prefer something else, or if you have any suggestions. Any of those would work. In the last episode, we got to this point where we have jumping working. We can spawn power-ups, and we can spawn flowers, and we can power Mario up appropriately and everything, and it all works good. And then the mushroom has some basic AI so that if it hits a block, it just sort of turns around and continues moving along. In this episode, what we're going to be doing is implementing the Goombas and possibly the turtles and changing the background color of the camera. So let's see how much of this we can get done. First thing I'd like to do is let's go into our scene, and we're going to do a couple things. Not the scene initializer, but the level editor initializer, or whatever it's called. So I want to do a couple of things. First of all, when we open up our menu, we have all of the blocks here, but this is kind of stupid because first of all, I don't want to place a block like that and be able to run into it. Like these all have default bounding boxes and stuff. And also there are some blocks missing that we could be using, but we're not, because I stopped before we got to like all the decoration blocks. So, and then for instance too, this is a decoration block. You shouldn't be able to collide with this, but it gets a default collider added to it anyways. So basically what I want to do is I just want to add in a way to not add decorated blocks as like collision blocks, and then add a new tab up here that's basically just decorations. So we're going to do all that, and then we're going to add a Goomba to the prefabs after we get that done. So first of all, let's change this from blocks to solid blocks. And it's going to get a little crazy in here because I basically just hard-coded in when to stop, when to go. And I think we have this correct. This all looks good to me. Okay, yeah, that all looks good to me. So we'll just simply go down here, and then we'll say if ImGui.begin tab item, decorations, or decoration blocks. We'll do this, and then we'll just say ImGui.end tab item, just so that we don't forget to do that. And then we'll add in all the decoration blocks into here. Now to do that, I am literally just going to copy this because it's going to be very similar. So we'll copy all of that, and then we'll just paste it right here, and we might have an, nope, okay, that's good. Cool. And technically you could extract all this into like a separate function, which would probably be cleaner than what I'm doing. So if you want to write some better code than me, I would suggest doing that. Now, instead of going from 0, we're going to start from 34 because that's when all the decoration blocks start. And we're just going to stop at 61, which is when the decoration blocks stop. And then right here, we're going to say if I is greater than or equal to 35 and I is less than 38. We want to skip all of those blocks. And then we also want to say if I is greater than or equal to 42 and I is less than 45, skip all of those blocks too, because those are all just solid blocks. So we don't want to duplicate them into the this area. Okay, and then when we go ahead and push the ID, we can get rid of a lot of this because we're not going to have these be physics objects, so we don't need the rigid body. We can get rid of that. We don't need a box collider, so we can get rid of that. And these are not ground, so we can get rid of that. And there are no breakable bricks, so we can get rid of that. So we should just be left with those two things, and that should be good. So if we go back in, we should have a new tab, which is decoration blocks, and then we can go ahead and add stuff from this tab. And so if I just add a few of those, and then I'm actually going to delete that, then we should be able to run right through this. And sure enough, we can run right through that. Cool. So that's going to be nice just for the future when we go ahead and actually implement decorations if you want to. If you don't want to, you know, do whatever you want. This is your engine. This is just a tutorial to teach you how to do what I did. So you can change it however you want. Anyways, we're going to have to add a new prefab. So we have generate Mario right here, then we have generate question block, and I would like to say, let's create a generate Goomba. So basically we're just gonna sort of copy this stuff. I think that's gonna be pretty good. So we'll just copy all of that. We wanna make sure we do it on the same line because this is just the third thing we're adding here, so we shouldn't be overrunning the line width or anything like that. Let's also go ahead and say ImGui.pop ID. That way we get rid of the ID that we had pushed for this guy, and we didn't actually push an ID for that guy. So this is important because we're going to be using some of the same textures again. So let's go ahead and we're just going to say ImGui.pushID here, UID++, and then we're going to say ImGui.popID. And it looks like we didn't do this at all actually. So we're basically just going to create a UID or a unique ID, which will be used just to make sure that if we use two images from the same texture, we don't like end up linking that to the same button, right? So we just sort of create a fake ID for ImGui for this tab, and then we just assign a unique ID for each of these things. And if we do UID++, that means that it changes every time we use it. So we can simply do that, and then right here, we're gonna say ImGui.pushID UID++. Once again, it'll change the ID. And then right here, we'll also say ImGui.pushID UID++. I feel like we use this in one of the above parts of this giant function. I just can't remember for sure. So then the Goomba, we do not need to get a new sprite sheet because he has his sprite inside of the player sprites. And so we'll just say his sprite is playersprites.getSprite14, which should give us the Goomba. So that's the texture ID. All of that stuff should be fine. And I believe the rest of this should be good, except we just want to change this to generate Goomba, which should give us a Goomba once all is said and done. So let's go into prefabs now. And inside of prefabs, I'm going to go ahead and copy. Let's copy block coin, because I feel like this is going to be pretty similar to what we'll need, and we'll change it appropriately. So I'll copy that, and then I'm going to call this generate Goomba. And for now, it's just going to generate a block coin, which is fine because I just need to make sure it's working. So if we click into prefabs, no, it's not working. See, this is why we test things. It says size of stack, window ID stack. We missed a push or pop ID. So it looks like I missed it. I thought I was being careful, but not careful enough. Let's see what I missed. So we have ImGui end tab item here. Oh, and I see what the problem is. I never popped this ID. Always pop your IDs. Okay. So with that done, we should be good. And if we just click onto prefabs, okay, cool. So we see the Goomba pop up. It's not, yeah, you see it played a coin noise and we actually got a coin. That's kind of cool actually, but that's not the behavior we want. We want to actually generate a Goomba. So let's go ahead and implement that so that it actually works. Let's go back into prefabs, and we're going to change this to be the, we'll just call it sprites. It's the player sprites and the enemy sprites. And then we'll just change this to be spritesheet.png. Then we're going to call this Goomba because this is not a coin, and we're going to be getting sprite 14 for this Goomba, and the default size 0.25 is good with me. So the Goomba has two animation states, right? He has the walk and the squashed animation. So I'm just going to change this, and we're going to call this walk. It doesn't need anything special. 0.23f was good for me. And then from this, we just have 2 frames. So I'll just copy that, paste it over that, and then we'll get rid of that. And we just want frame 14 and frame 15, and they both are going to use the default frame time. Cool. So that should be our walk animation done. And then we have one more animation, of course, which is going to be our squashed animation. Just set that to a new animation state. We'll say squashed title equals squashed. And then we'll say squash.add frame player, or actually just sprites, .get sprite 16. And we're just going to give that 0.1f. And we're going to say that this does not loop. Okay, cool. So those are the 2 animations, and we just have 1 transition because this is a very simple state machine. So we will say add the walk animation, and we also want to add the squashed animation to our state machine. And once we have both of those, we can set the default state to walk. And we'll say state machine.add state, or technically trigger. This function should really be renamed. So we'll say state from walk.title to squash.title on squash me, which is the trigger. And then we'll just say Goomba.add component state machine. And yeah, we don't really want any of these because Goomba is not a question block. But we do need a couple other things. The Goomba is going to have a rigid body because, of course, he needs to move. So we'll say rigid body 2D RB equals a new rigid body 2D. And we'll say rb.set body type to body type dot dynamic. So we're going to do something similar to Mario that with the Goomba. We can set the mass and everything, but I don't think this is going to affect it for real this time. So we should be good. I'm going to set the fixed rotation to true. And then we're going to say Goomba.add component RB. And then we're going to say circle collider circle equals a new circle collider. So we're going to do sort of similar to what we did with the flower and the mushroom. And then we're going to say circle.setRadius 0.12f and Goomba.addComponent circle. And then we're just going to return that Goomba. Cool. So we also need one more thing, which I almost forgot about. The most important thing, which is his AI. So we'll say add a new Goomba AI, which we don't have yet. So we will go ahead and create that very quickly. Call that Goomba AI. This extends component. And for now, he's going to do nothing. Oh, and that should be new Goomba AI. Okay. Cool. So with that all in place, we should be able to just spawn in a Goomba and he should just sort of waddle. Yeah, there we go. So he waddles, but he doesn't really do anything. And if we were to hit play, he has no logic associated with him because we didn't actually implement any sort of AI yet. So let's go ahead and delete that guy for now. And let's go into Goomba AI and actually implement some logic. Okay, so right now I am going to extract a little bit from our Mario player controller. So I'm kind of going off script here from what I did in my original code so that this is just a little bit nicer. Let's go into Jade and we'll go into Physics 2D and then let's just go straight into Physics 2D. And we're going to add a static function here. I guess it could be non-static. It doesn't really matter too much, but we'll make this static. And we're going to call this public static void. I guess this should return a bool though. Boolean check on ground. And this is going to take in a float inner player width and a float height. Okay, and we possibly need to add a game object in there too. Basically what we're going to do is if we go into Mario, or I guess player controller, he has this function called check on ground, and we just want to extract all of this logic because we're going to be using it in a few different things. So let's extract all that, and then we're going to put it inside of Physics 2D. So we'll just paste it here. So we do need a game object. We'll just pass in a game object as well, and we'll just call it game object. So this function takes in a game object, the player width, and the height. So we'll just change this to game object. We will get rid of this because we are now taking that as a parameter. And we'll set yval equal to whatever height they're using. Okay, and then we can set all of these a little bit differently. So yes, we can actually inline this. So I'm just going to say inline, and IntelliJ will automatically replace that for me, which is good. And then we'll just say instead of on ground equals this, we can just say return this. And now we have extracted that logic, which is good because now we can use it in several different things without having to worry. So if we go back into Mario or player controller, we should be able to change this up a bit. And actually let's keep these inside of Physics 2D just so that we can actually draw things and debug and make sure that everything is going correctly. So I'm going to leave this as it is, and then we'll just hit Alt Enter, import that, Alt Enter on Vector 3F, import that, and then we'll go back into player controller once again. And let's change this up to use this new function. So we will still need inner player width, so I'm going to keep that. We can get rid of that. We can get rid of that. We still need yval, and then we should be able to get rid of everything else. And then we can just say, instead of all of that, on ground equals physics 2D dot check on ground. We'll change it. We'll give it this game object. So I guess we should call this dot game object just so that's clear. For the inner player width, we'll just pass that. And for the height, we'll just pass y value. Okay, cool. So if we do this, we have just extracted that logic out, and we should still be able to play. You can see that, and you can see it shooting the raycast in the appropriate location. That's all good. Cool. So now we can go into our Goomba, and we can give him a similar functionality. So he will also have a public void check on ground function, which does something similar. And he'll have an inner player width, which equals 0.25f times 0.7f. So I just kind of tweaked values until I got something I liked, and that was what I liked. And then we'll say float yval equals negative 0.14f. And then we'll just say on ground equals physics 2D dot check on ground, this dot game object, inner player width, and yval. Cool. And of course, he's going to need a private Boolean on ground variable, which is false initially. Yeah, I'll leave that as false initially. And let's also make this transient. We don't want to serialize any of this data. Then he's also going to have a private transient going right, which is a Boolean, which is going to be false initially. So he's always going to start off going left. We could tweak that if we wanted to. We'll have a rigid body RB. We will also have a float walk speed. We'll have a private transient vector 2f velocity. So we're going to be sort of implementing these velocity things and everything ourselves again. And we could extract all this logic because it's going to be following our Mario player controller very closely, but you can do that on your own if you want to make your code just a little bit better. So then we'll also have acceleration and we'll have terminal velocity. And we've got that on ground variable. And then we'll have private transient. Boolean is dead, which is false initially. We'll have transient float time to kill equals 0.5f. So that's how long when he goes into a squashed animation state that will wait. And then we'll just have a reference to his state machine. And we'll just call that state machine. Cool. So we want to get references real quickly. So we'll say public void start, get a reference to the state machine, which we can do just by saying get component state machine dot class. Then we can say rigid body equals game object dot get component rigid body class. And then we'll just set the acceleration.y equal to window.getPhysics.getGravity.y times 0.7f. Same as Mario's. We should probably create a constant for that too, but like I said, I don't really care too much about this stuff. So we'll leave it as it is. And then we'll have a public void update float delta time. And one thing I did do is if the Goomba is to the right of the camera, I don't update it so that he doesn't start walking until we run into him. So we're going to get the camera real quick. We'll say camera equals window.getScene.getCamera. Or I think it's just called .camera. And we'll go ahead and import that. Then we'll say if this .gameObject.transform.position.x is greater than camera.position.x plus camera.projection size.x times camera.getZoom, which that should give us basically like the width to the right edge of the screen in world units. So that's good. Then we'll just say return. Okay, so basically if the camera's to the right of us, we're not going to update this Goomba. He's just going to do nothing. Okay, and then we're going to say if we're going right, then velocity.x equals walk speed. Else velocity.x equals negative walk speed, right? That's pretty straightforward, self-explanatory. Then we'll just check if we're on the ground. Then we'll say if we're on the ground, this.acceleration.y equals 0. This.velocity.y equals 0. We don't want to be moving vertically if we are on the ground, so we'll just reset those. Otherwise, this.acceleration.y equals window.getPhysics.getGravity.y times 0.7. So 70% of box2D's gravity. Then we can say this.velocity.y plus equals this.acceleration.y times dt. This.velocity.y equals math.max. Math.min. This.velocity.y terminal velocity.y and negative terminal velocity.y. Okay, so that's very similar to what we did in player controller. We're just kind of clamping the y velocity to terminal velocity. We don't have to worry about the horizontal because we're setting that manually. And then we can just say set the velocity in the rigid body to our velocity. Cool. So that should be good, except we have a problem because the Goomba is just going to move left, right? If we were to run this right now and we just plop a Goomba down into here, technically he should move left. Something must be going wrong. So let's see what's happening. And I just did some simple debugging. He's not moving because what is walk speed? Well, walk speed is nothing. Yeah, it would be smart of me to actually initialize that before we try to use it. So what should walk speed be? Well, it should be 0.6f. That's the one that I came to and I liked. Okay, so now if we run this, there we go. So our Goomba dutifully goes towards Mario to try and kill him.
Unfortunately, he's just going to hit Mario and nothing's going to happen because we don't have anything else programmed in. He's just going to push Mario along. So let's go ahead and make it so that, first of all, if the Goomba hits a block, he turns around. And then second of all, if he hits Mario, he kills Mario. So we'll go ahead and override our begin collision method. So we'll say public void begin collision, game object, obj, contact, and vector2f contact normal. We'll say if we're dead, return. So if we're dead, we don't want to really do anything. Let's import that. And then we'll say player controller equals obj.getComponent player controller.class. If the player controller is not null, so meaning we hit the player, then what do we want to do? Well, we want to say if the player controller is dead. So if the player controller is not dead, and that is not a function, so let's go into player controller very quickly and just create a function that just says public boolean is dead, return this dot is dead. Okay, you go back into the Goomba. So if the player controller is not dead and the player controller is not hurt invincible. Okay, so this is a function we'll create, which is basically the player controller is sort of like in that phase where he just got hit by somebody. So he's invincible for a certain amount of time, or he's just invincible. That's what that checks. And the contact normal dot y is greater than 0.58f, which means, and that should be contact normal. So what is this saying? Okay, this is saying if the player is not dead and the player is not invincible for any reason, and the contact normal is greater than 0.58 in the y direction, which means the player jumped on top of the Goomba's head. That's what this means. Then we'll say player controller.enemy bounce, which will be a function we implement in a second. And then we'll say stomp, which is another function we'll implement in a second. And do we actually have enemy bounce? No, that's just, okay. Yeah, that's poorly named on my part. I named functions the same thing as I named the variables, which isn't very good practice. But we'll just comment these out for now. But basically, this is just going to execute whenever our Goomba gets stomped on. Otherwise, if the player controller is not dead and the player controller is invincible, which is something else we'll check for. So if the player controller is not dead and he's not invincible and he hit us, the only alternative is that he hit us with like a contact normal less than this, because otherwise we would have entered into here. Then we'll just say player controller.die, which is another function we will implement in a second. So if we hit the player controller on the sides, we kill him. And then we'll say otherwise if we are not hitting the player controller, if the math.absolute value of the contact normal.y is less than 0.1f, meaning we hit something on the side, then we'll say going right equals contact normal.x is less than 0. Okay, cool. So let's go ahead and implement is hurt invincible and is invincible very quickly in the player controller. So if we scroll all the way down, we can go ahead and just say public boolean is hurt invincible, which will just say return this dot player state, or I'm sorry, return this dot is hurt invincibility time left, and that's a big word. I don't know if I spelled that right. I think I did. Is greater than 0. So this is a variable we will go ahead and implement. Just hit Alt Enter, and then we'll say create field inside of player controller, and this is just gonna be an int, and we're gonna initialize that to 0 for now. So I'll go ahead and move that down here somewhere. We'll just move it here, and we'll make this transient. So if they are hurt invincible, then, you know, we'll check that. And then for public boolean is invincible, this will just return this dot player state equals player state dot invincible, or this dot hurt invincibility time left is greater than 0. Okay, so that will just check and see if either of those are true. Cool. So if we go back into Goomba, we have no problems there anymore. If we run this, our Goomba should turn around once he hits a block. If he hits us, it's not going to do anything because technically we should die, but we don't have that implemented yet. So he just kind of pushes us. But if we go ahead and place a block there and he hits the block, he should hit it and start walking back and forth. Cool. So that is Goomba AI, almost done. Let's go ahead and implement these extra methods, which is enemy bounce and stomp. We'll do those first, and then we'll do the player controller.die. So player controller.enemy bounce is actually going to be pretty simple. If we just go into here, we can say public void enemy bounce, and this is going to say this.enemy bounce equals 8. And I don't believe we use that in our jump physics. No, we did not. So if you just scroll up to where we are doing our jump physics for the player controller, we're going to have to change it up a bit to incorporate enemy bounces. This is fairly simple. So we just check and see if the player is pressing the bounce key. We do all that stuff if we are. Otherwise, if enemy bounce is greater than 0, which means he is bouncing for a different reason, fix that very quickly. Then we'll say enemy bounce minus minus this.velocity.y equals enemy bounce over 2.2f times jump boost. All right, so it's literally just these two lines except applied to enemy bounces. So that'll give us a little bit of a hop so that when we jump on the Goomba, our player just sort of bounces a very little bit and it's predictable. It should be the same every time we hit the Goomba, which is good. Okay, and for the stomp function, we'll just go down here and we'll say public void stomp with no parameters, and then this is going to call an extra function, so we're just going to overload a method, and this is going to say boolean play sound. I'm not sure why I overloaded this, but we'll probably find out in the future. But anyways, this is just a way in Java to overload a method with some default values, so that if you call it with no parameters, it just calls this with true by default. So we'll say this.isDead is true. We're clearly dead now. This.velocity.0, so we zero our velocity. This.rb.set velocity to a new vector f. So we zero our rigid body's velocity too. This.rb.set angular velocity to 0. So if it had any angular velocity, that should be gone. This.rb.set gravity scale to, I think that should be 0. Yep. So no gravity is affecting it anymore. That should already be true, but just in case. And then we'll trigger squash me for our state machine, which should tell us to switch animations. We'll say rb.set is sensor. So we should turn into a sensor, so no collision should happen anymore. And then finally, if we want to play the sound, we should say asset pool dot get sound assets slash sounds slash bump dot ogg dot play. All right, so it just does a bunch of different things, which basically just checks to make sure that we have all of these appropriate stuff set. So then if we were to play this, he should switch state machines and we cannot collide with him if we jump on top of him. And we should do a little, yeah, so we hop on him and it almost all works correctly. He keeps moving though, so that's wrong. And why does he keep moving? Well, it's because we never checked for if he's dead inside of this function. So his going right resets the velocity and everything. So we should check and see if it's dead inside the update function so we can handle that. So let's say if he's dead, we'll say time to kill minus equals dt. If time to kill is less than or equal to 0, then this.gameObject.destroy. So we just kill it after 5 seconds and then we return. So this way we shouldn't reset his velocity and then his body will disappear because we don't want the carcasses of our enemy on our screen. Okay, so that's almost correct, except he kind of floats away. So we can fix this just by saying this.rb.set velocity to a new vector 2f inside of the isDead function. I'm not sure why we need this. I would have to do more debugging to see what I may have missed that is causing that, but yeah, that should fix it and we're all good there. Last thing I'm going to do for this episode is implement the player controller's die animation, which is a little bit more involved. So let's go into our player controller and we'll go ahead and add a new function inside of here. We will just say public void die. We'll say this.stateMachine, first of all, trigger die, which should do the correct animation. And that should basically just downgrade us if we're Big Mario or Fire Mario. And then if we're Small Mario, it should send us to like the actual death animation. So this doesn't actually kill you. It just sort of hurts you. So I guess a better name for this function will be hurt. But we'll say if this.playerState equals playerState.small. Then we'll say this.velocity.set 0, 0. This.acceleration.set 0, 0. I guess we could just say 0 those. And then this.rb.set velocity, new vector 2f. this dot is dead equals true. This dot rb dot set is center. So very similar to what we did for our Goomba just a second ago. We'll say get sound assets slash sounds slash Mario die.ogg dot play. So we play the death animation or the death sound. And then we'll say dead max height, which is a variable we'll create in a second, is this dot game object dot transform dot position dot y plus 0.3f. Because what happens to Mario when he dies? Well, he goes up, then he goes down. So we're basically going to say, okay, go up to this position and then fall back down. And we're going to do all that manually in just a second. Then we'll say this dot rb dot set body type to body type dot static. So that should stop all physical forces from acting on it. And then we'll say game object dot transform dot position dot y is greater than 0. We'll say dead min height equals minus 0.25f. This will just ensure that if we're not already below the screen, we have to go below the screen to end the death animation. Okay, we'll fix all that stuff up in a second. We'll say otherwise if this dot player state equals player state dot big. We'll say this dot player state equals player state dot small. So we'll just switch to a small state. We'll say game object dot transform dot position or dot scale dot y equals 0.25f. So we go back to small Mario. Then we'll say pillbox collider pb equals game object dot get component pillbox collider dot class. So we basically just have to reset the bounds on this guy. So we'll say if that's not null, jump boost divided by equals the big jump boost factor, walk speed divided by equals the big jump boost factor, which I think we used, and then pb.setHeight 0.31f. So we just sort of reset everything. And then we'll say hurt invincibility time left equals hurt invincibility time, which is like the basic time we get to be invincible for. And we'll initialize all that stuff in just a second too. We'll say otherwise asset pool.getSound, assets slash sounds slash pipe.ogg.play, which is weird, I know, but that is the sound they play whenever you get hurt in Mario, which I didn't know until this. And then finally, we'll say if player state equals player state dot fire. Then we'll say this dot player state equals player state dot big. Hurt invincibility time left equals hurt invincibility time, which we'll implement in a second. And then asset pool dot set, basically this thing. Okay, so just copy that. It's kind of funny as Mario is in bigger states. The stuff you have to do when he gets hurt is easier, which is weird. It's like the inverse of what he's actually doing. Anyways, with that aside, let's go ahead. We'll say create dead max height, min height, and hurt invincibility time. So if we go up to the top, right before this, we'll just copy that first of all so that we can get that in there. And let's actually change these to floats. So that'll be a float and that will be a float because this is going to be in seconds. 1.4 seconds is how much invincibility time you get. Then we'll say private transient float dead max height equals 0. Private transient float dead min height equals 0. Private transient boolean dead going up equals true. So the dead going up is basically like, are we moving up in the dead animation, which we'll be using in just a second. And then we'll also have a private transient float blink time equals 0.0f because Mario also blinks when he gets hurt. So we have to make sure we implement all of this. So this is where our player controller just starts getting very complicated. So inside of our player controller, before we do any player checking, we'll say if we're dead, we need to do something else. We'll say if this.gameObject.transform.position.y is less than the dead max height and we are going up, then we want to keep going up. So we'll say this.gameObject.transform.position.y plus equals dt times walk speed over 2.0f, which is just a value I found that worked good. We'll say otherwise if our y position is greater than or equal to dead max height and we're still going up, then we need to start going down. So we'll say dead going up equals false. And then we'll say otherwise if we're not going up and our position.y is greater than the min height, then we need to keep going down. So we'll say this.rb.set body type kinematic. Not sure why I did that. Maybe I was having problems. Then we'll say this.acceleration.y equals window.getPhysics.getGravity.y times 0.7f. Oh, so we basically just reset it so that we're moving with gravity again, which should be good. And we'll say this dot velocity dot y plus equals this dot acceleration dot y times dt. And we'll say this dot velocity dot y equals, I'm going to grab this because I don't feel like typing all this out once again. It's just going to be this. So copy that, paste it. We're just going to clamp it to terminal velocity, which is good. So clamp it to terminal velocity if we need to. And we'll say this dot rb dot set velocity to this dot velocity, set angular velocity to 0. Okay, so that's if we're going down. Otherwise, if we're not going up and our transform position y is less than or equal to the min height, we have finished, we are dead, we're off the screen. We'll say window.change scene to a new level scene initializer. So this should basically just change us back to the original scene and stop the game. We'll see how that works. And then finally return. I want to make sure we return. We also have to deal with if we're hurt and we're invincible for a little bit. So we'll say if hurt invincibility time left is greater than 0, hurt invincibility time left minus equals dt, blink time minus equals dt. If blink time is less than or equal to 0, so we basically want to blink on and off, we'll say blink time equals 0.2f if sprite.getColor. We need the sprite now too, so let's get a hold of that. We'll say private transient sprite render SPR. And then inside start, we'll say this .spr equals GameObject.getComponent sprite render.class. So we'll simply change the color so that we look like we're blinking. We'll say sprite.getColor. If the W component is 1, we'll say sprite.setColor. New vector 4f 1110. So we basically just blink Mario off if he's on, and then if he's not, then we'll say else sprite.setColor, new vector for f 1111 instead of 0 for alpha. So you should blink on and off. Otherwise, if we're not blinking anymore and Mario's color.w is 0, we just want to make sure we reset that to 1. So we'll say reset it to 1111. That way he's back to color. Okay, so if we run this, it should work, hopefully. Let's see. If we hit this Goomba, we get the death animation sound, he plays, and then we get the level reset. Cool. So I was not expecting that to work first try, but it did. That's great. Okay, so then if we hit that, we get turned into Hurt Mario, and then we sort of blink there. We should be running through the Goomba, but you know, I'm fine with that. I think that's pretty good for now. So like basically we just blink for a little bit, we're invincible, and technically we should fly through the Goomba, but you know, doesn't matter too much to me. And then once again, if we just hit the Goomba, so I guess it would be easier if I just remove this block. If we just hit the Goomba, we die. Cool. So in the next episode, because this has gone on for a pretty long time, maybe we'll implement the turtle AI and try and get camera movement working and the camera color working and everything. And we also need to get Z-index working. And I think that should be like almost the rest of the game. The only other big thing that we haven't done is pipes. So, you know, I'll try and get those done too. If you remember in the last episode, we left off here where we basically have a little scene and Mario can run around, jump on enemies, kill the enemies, and all that good stuff. In this episode, what I want to do is get the pipes into place so that we can lay down different pipes and we can enter through one pipe and then we'll exit through a different pipe. So in order to do that, we're going to have to come up with a little bit of a system that will make this easy on ourselves. So let's take a look at some drawings to see how we can create a system that will make this work with the engine we have. All right, so imagine for a minute that this is Mario and this is a Mario world, and these pipes are actually Mario pipes, not the bad drawing that I have here. So if we want to connect these two pipes together, think about how we could do that with the engine we have. Right now, there's no real good way to reference game objects, but we do have one function, which is get game object by name. So if we give this pipe a name, say pipe 01, and then we give this a pipe another unique name, say pipe 02, we could connect these two pipes through a reference obtained at runtime, right? We could basically say, okay, I want this pipe to grab a hold of this pipe at runtime, and they are connected to each other.
Now, that's the pretty easy part, but then how do we determine where to place Mario? If Mario jumps up onto this pipe right here, first of all, how can we tell when he presses down? Well, we can tell when he presses down just by checking for which key, but let's change this up a bit. Say there's another pipe, because this does happen in Mario, that looks more like this, and we want Mario to go through when you press the right arrow key. Well, now we need a way to determine which direction the pipes are facing, and we also need a way to determine which side of the pipe Mario is on. We already know we can tell which side of the pipe Mario is on pretty easily. I'm going to erase this real quickly. If Mario is on top of this pipe, we know that the physics engine will tell us that there's a collision happening between these two objects. In which direction the collision is going to be facing will depend on the object. So if we're looking from the pipe's perspective, we're going to be getting a collision pointing downwards because that's the direction that Mario is trying to push the pipe. But if we're looking at Mario's perspective, we're going to be getting a collision going upwards because that's the pipe that Mario is trying to sit on the pipe. So we can simply check for the collision normal and see which direction is the highest. Now we have to be careful because Mario could hit the pipe at a direction. If he's running to the left, say, and he presses up, then we could get a slight vertical velocity. And so even though there's a slight vertical, we know that this is actually a horizontal hit because you can see from the direction that it has more horizontal velocity than vertical. And this is why we always make sure that we have a threshold value when we're doing our Box 2D normals, because Box 2D could give us something that looks slightly like this. Clearly that is a normal that we would want to count, but we just have to make sure that it is above a certain threshold. And so if you accept anything a little bit too low, say something like this, that might not actually be true because he could just be sliding over the edge of the pipe. So using this same concept, if Mario is running into this pipe, he'll have a normal hitting out this way. And from the pipe's perspective, Mario will be running into it. So we can check the normal to determine which direction Mario is facing. And then once we do that, we can figure out, well, if it's left, then when Mario presses the right arrow key, or D, if we're using WASD, enter the pipe. Then to make Mario enter the pipe, we simply move his transform from here through the pipe here. And then what we can do is we can just use the pipe's position plus a certain value. If the pipe exits on the bottom, then we move Mario down. If it's on the top, then we move Mario up here, right, left, so on, so forth. So we simply need to come up with a mechanism to give pipes directions, which I represent using an enum, which I think I called direction or something or other. And this direction enum just has 4 values: up, down, left, and right. So we can have pipes facing up, down, left, or right, and we can encode those through specific prefabs that we generate inside of our prefab class. And that is most likely the direction we will take with this, no pun intended. So let's jump into the code and see how this works. All right, so I am back inside of our level editor scene, and we have a certain sprite sheet here called pipes, and you'll notice that it's size of 32 by 32, which means that it's twice as big as the normal sprites, which are usually 16 by 16. So we can just use these to create some special game objects inside of our prefab section. So we have the decoration blocks, and I'm going to scroll down to where we have our prefab selector inside of the level editor scene initializer. And if we scroll down, I'm just going to place these after our last item here, which I believe was the Goomba. So we'll just add in another few lines of code here. We'll say sprite sheet pipes equals asset pool dot get sprite sheet assets / images / pipes dot png. And then we can literally just copy this because we're going to be doing pretty much exactly the same thing here again. Once again, you should probably extract this out into its own function since we do the same thing so many times. The only difference is we're going to be getting sprite 0, and we're going to be getting it from the pipes sprite sheet, not the player sprite sheet. Then we'll get the texture ID. We will get push a unique ID. We will get the texture coordinates, and we'll simply do the same things here. And then lastly, we're going to say generate pipe for our prefabs, and we're going to create this function in a second, and this will take in a direction dot down, which we're going to implement as well in a second. So this will basically generate a pipe with the direction down, which is the same as this picture. Let's also make sure that we don't forget to add in ImGui.SameLine here, and ImGui.SameLine right here as well. And then let's go ahead and add a few more. Actually, we can just copy right up to here. And this will be for the other pipe. So we'll add 1, 2, 3 more. And this will be 0, then 1, 2, and then 3. And for 1, that is the picture of the pipe facing up. For 2, that is the picture of the pipe facing right. And for 3, that is the picture of the pipe facing to the left. So that should be all of our bases covered. And I'll remove this same line here so that we don't get any weird things when it comes to the next tab. And as for this direction class enum, let's generate that real quickly. We can just scroll down to editor and we'll go ahead and add a new Java class, then just hit enum instead, and we'll call this direction. And like I said, we can just have this tab up, down, left, and right, which should be all we need. And I put that in the wrong package. We want this inside of Jade, so just move that over if you made the same mistake as me. And then we can click on this related problem, and that should be cleared up. So we should have no errors inside of here, and we should have no errors inside the main file as well. All right, let's go into prefabs now so that we can create this generate pipe function. And I'm actually going to copy one of these smaller functions because once again, we're going to be using some very similar states in everything for this. So I'll just copy the block coin and we'll be able to simplify that a bit more. And I'll scroll all the way to the bottom. There we go. And we can take in, for the generate pipe function, we will take in a direction, and this will be the direction of the pipe. So we'll say that our sprite sheet is our pipes, and we'll say get sprite sheet pipes.png not items. And then we can create like a little helper function to get the correct index for the correct image. We'll say if the direction is equal to direction.down question mark. This is just a ternary statement. If that's true, then we'll use index 0. Otherwise, which is what the colon is, we can use direction equals direction dot right. If that's true, then or actually I'll do up so that we do this in chronological order. We'll use 1. Otherwise, if direction equals direction dot right, we can use 2. Lastly, otherwise, we can use if direction equals direction dot left, we'll use 3. And otherwise, we'll use -1, which should throw an error. We should never get that, but just in case it somehow magically happens, we have that base covered as well, and it should throw a runtime error. We can make that a little bit safer as well, and we can say assert index does not equal -1, invalid pipe direction. And that just makes sure we have a little bit extra protection there. We know what should happen, and this will give us a little message in case that does happen. And then we'll just say that this is going to be pipes.getSpriteIndex. And we want to change the size too. So right now we have these at 0.25, but we actually want these at 0.5 since all the pipe sprite sheets are actually twice as big. So we're just going to do that to make it a little bit easier. We don't need any state machine, so I'm going to go ahead and remove all of that animation state. I'm just going to go ahead and remove all of that actually. Okay, and then let's finally call this a pipe because that is what it is, and we'll return a pipe. So what do we need? We need a rigid body first of all. So we'll call that RB equals a new rigid body. We're going to say rb.setBodyType to bodyType.static. The pipe never moves. It stays in one place the whole game, so we can do that. We'll set the fixed rotation to true. We'll set continuous collision to false. And then we'll say pipe.addComponent RB. Fixed rotation and continuous collision shouldn't really do too much. Continuous collision might be important, but it's not moving, so it doesn't really matter. We should have really initialized continuous collision to false since that is the appropriate value for most objects. Next, we're going to use a box2D collider to represent the pipe. So we'll say box2D collider b2d equals a new box2D collider. Then we'll say b2d.set half size to 0.5f 0.5f, which is going to be a new vector 2f. And that should give us the correct bounds, and we'll add that component to our pipe. Finally, we want to add in a component, which is a new pipe, and we'll give it the direction. So that's going to be sort of our pipe component. And we also want to make sure we add in a ground component. That way Mario can walk on it. Now, we don't actually have a pipe object, so let's go ahead and inside of components, we'll create a new class and call this pipe. This pipe is going to extend component. And for now, we're going to leave it empty. We may as well add the constructor. So we'll say public pipe direction, just so that we have that. And then we'll store that as a private variable, private. And this won't be transient because we do want to keep this. And then we'll just say this dot direction equals direction. There we go. Now, if we go and run this, we should be able to add pipes into the game. They won't really do much, but it will allow us to at least add them. So if we hit prefabs, you can see we have the pipes. If we hit this block here, you can see I get this pipe added into the game. We will have to fix how this is added because right now it's sort of in the middle of the blocks. So we will fix that up in due time. All right, so inside of our pipe class, we'll go ahead and add some member variables that we will need. First of all, we will need a string, which is going to be our connecting pipes name. So that will be the name of the game object we connect to. We, of course, want to serialize that because we want to save it. We also want to mark whether this is an entrance or not. This will be good because this way we can mark which pipe you go in through, and you can't go in through the exiting pipe. This is just because if you want a one-way pipe, you need to make sure to mark that. I think with this system, you could also have two-way pipes if you want to, which is cool. We also want to make a transient game object, and that will be the connecting pipe, which is set to null initially. And we will also have a transient float entrance vector tolerance, and this is basically that tolerance I was talking about. We just want to make sure we're above a certain threshold before we say that the player can enter, and that's where we set that value. And we'll have a private transient player controller colliding player. And that will just keep track of the player whenever he collides against us. Okay, inside of our start method, we will want to make sure to get a hold of that connecting pipe. So we'll say public void start, and then we'll say connecting pipe equals window.getScene.getGameObject, and we should be able to get a game object by name, but we don't actually have that yet. So let's go ahead and add that function. So if we go into getScene, and then if we go into the scene class, we can scroll down where we have our other getGameObject method, and we can create something very similar. So if we just copy this, we're basically going to want to do the same thing, except we will use a string GameObject name. This way we can get game objects by name if we wish. And then we can just make sure that the game object's name is equal to that game object name, and make sure to use dot equals because Java does not like using the equality operator since you can't overload that. This will return the game object or null. And if we go back into here, we just need to add in the game object now by saying connecting pipe name. That should give us a reference to the actual game object. Next, we want to do the update method, which is going to be kind of difficult. It's not very difficult, but it is a little bit more complex than the last thing. The first thing we'll want to do is say if the connecting pipe is null, just return. And this is just so that if we, for whatever reason, did not get a connection properly, we don't get any null errors. Maybe you would want to log a warning in here or something. That's up to you. Okay, and then the next thing we want to say is if the colliding player is not null, which means we have a player that is colliding with us right now, we're going to switch on this pipe's direction. And depending on which direction the pipe is, we'll check and see if the player is pressing the appropriate key to get into the pipe. And if he is, then we will just make him travel through the pipe, quote unquote. So let's say case up. If the player is on a pipe that is facing up, we'll say if the key listener dot is key pressed GLFW key down, and we'll go ahead and import that from LWJGL, or inside these parentheses, we'll say key listener dot is key pressed GLFW key S. So we're basically just going to support WASD and arrow keys, and then we'll say and this is an entrance. So we'll say if they're pressing the appropriate key and this pipe is an entrance pipe, then we basically want to make sure that they travel. Let's import this as well, and that should be good. And I'll just move this down a little bit more so that we can sort of see this. We'll want to do something basically exactly the same for all the other things too. So let's just break here. Then we'll say case left. If we're going left, what do we want to do? Well, if they're pressing the right key, so key right, or if they are pressing the D key, so GLFW key D, we should do the same thing. Let's go ahead and import these, and now now IntelliJ has imported everything for me automatically. So then we'll say case right. Basically, we want to do the exact same thing. Copy that, and we'll say case down. Same thing. So if the pipe is facing the right, we want the key left, and we want key A. And if it's facing down, we want the key up. So up arrow key, or we want the key W. And that should cover all our bases. Now, how do we actually enter the pipe if the player is collided with it? Well, we can just set the player's position to this pipe plus the player's height, right? So we can literally just say colliding player dot set position, which we will add in a moment. And so we'll say set position to get player position, which is another function we'll create connecting pipe. So that should get the player's position and then set the position appropriately. And we'll also want to make sure to play the pipe sound. So we'll say asset pool dot get sound assets slash sounds slash pipe dot ogg dot play. And I just realized that we could actually simplify this quite a bit. So let's go ahead and simplify this because all the rest of my switch statements are exactly the same. So we'll say player entering is false. And the reason I'm doing this is because basically we're going to do this exact same code in each of these switch statements, which is kind of useless. So let's copy this, and then we'll just say player entering equals true. Then let's paste this below the switch statement, and we'll say if player entering, then we'll do that. And we can just go ahead and mark player entering as true in any of these cases, which should make sure that we enter this. So if the player is entering the pipe, we just set the position accordingly to whatever this pipe is. So we say set position to get player position, which we will create pretty much now. So let's go ahead and implement get player position. This will be a private vector2f get player position. And this is going to take in a game object, which is another pipe. So we'll say pipe component equals pipe dot get component pipe dot class. This should get us the pipe component. And using that, we can figure out which direction the other pipe is and get the appropriate amount that we need to go based on that. So we'll just say switch pipe components direction. And we can say case up. So if we're facing up, then we'll return a new vector2f pipe.transform.position.add 0, 0.5. So we're just going to add the pipe's height to Mario, and then we'll basically do the same thing for all the other cases. Left is going to be the same exact thing, except we want to do negative 0.5 and 0 because we know the pipe's heights and everything. And then case right, we want to do basically the same thing, except we'll add positive 0.5. And for case down, we will do the same thing, except we will add negative 0.5 to the y values. If all else fails, we'll just return an empty vector2f, which should add nothing to the player's position, thus setting it basically the same place. This is basically just going to set it to the connecting pipe, which is the pipe we want to go to, and then it's going to add the correct offset depending on which direction the connecting pipe is facing, which should give us the correct thing. Now let's go ahead and implement set position very quickly inside the player controller. This is actually really simple because we just want to make sure that we set the position inside of here so that the physics engine gets updated properly. So we'll say set position. This takes in a vector2f, a new position, and this will just say this.gameObject.transform.position.set to the new position, and it will also say this.rb.set position to the new position. That way the physics engine gets updated appropriately, and this means we need to go into the rigid body as well and add it into here, which we can do pretty easily just by saying public void set position vector2f new pose, and we'll say if raw body does not equal null, then raw body dot set transform new vec2 new pose dot x new pose dot y and 0 for the angle, which I guess we decided that this could just be the game object's transforms angle or rotation, which should be good as well because that should be 0 for the entirety of the game anyways. And with that done, you should see that we get this set as well. Now this will all work good inside of the update method, but that's assuming one thing, which is we have this colliding player variable set, which it's not because we don't know when the player is colliding with the pipe. Well, how can we know when the player is colliding with the pipe? And that's pretty easy. We already know that we can just override our collision method. So we'll simply override our public void begin collision method
which takes in a game object, colliding object, a contact, and a contact normal. And this should be very familiar to you by now. I hope you guys can appreciate the importance of these collision methods that we set up in the previous episodes. So right here, we'll just say player controller equals colliding object.get component player controller dot class. Okay, so we get a hold of the player controller, and if it's not null, meaning that the player has collided with this pipe, that's what this means. Then we'll switch on the direction, and we'll say if we're a pipe that's facing up, we'll check and see if the player is hitting us going down. So we'll just say if contact normal dot y is less than the entrance vector tolerance, meaning that the player's normal is pushing up compared to us, then we will just return. And that is because it's not actually meeting our tolerance yet. If it's greater than that, then that means we are actually having the player push down on us appropriately. And then we'll break. We'll say case, right, if the contact normal.x is less than the entrance, then we'll return. Otherwise, we will break. Then we'll say case down, almost the same thing. If contact normal.y is greater than negative entrance tolerance vector, we return. Otherwise, we break. And then we'll say case left. If the contact normal.x is greater than negative entrance, then we'll return. Otherwise, we break. And this is sort of just a way to return early. It just makes the code a little bit cleaner in this specific instance, which is why I chose to do it this way. Then we'll just say colliding player equals the player controller, which means we now have a reference to the player controller if they have indeed collided with us. Now this is all good, but we want to make sure that we end the collision, because what if the player turns away from the pipe? Then we want to make sure to mark that as well. So let's go ahead and actually copy just these two lines, because we can override the end collision method, which we haven't actually done yet. So we'll do that, and then I'm going to go ahead and close off that function, and we'll call this end collision instead. Takes in the same parameters, but now it's telling us that the collision is ended. And we will just copy these two lines of code as well, and we'll say if the player controller has collided us, then colliding player equals null. So basically, this just means that if the player was colliding with us but is no longer colliding with us, then we just set it to null. So that should be pretty simple, and it should do everything we want it to do. Let's go ahead and see if this works the way we think it should. So I will go ahead and grab a couple of prefabs. I'll have an entrance pipe right here. And this is going to look weird for now until we can fix the spacing. And then I'll add an exit pipe up here. So I'll call this entrance pipe. We can go into the pipe component. We can see it's facing up. You could change the direction if you want, but it doesn't make much sense. And we should have a way to input the name, but we don't. And why is that? Well, that's because I believe we haven't implemented a text box for strings yet. Yeah, because we have this string and it's not marked as transient, so it should be exposed, but it's not. We can do that pretty simply just by going into component, and we will go up to where we have our ImGui function, right? And you'll see that we don't actually handle the case for a string here, so we can just add that below type is enum. We'll say else if type equals string.class. So this means we just have a string. We can say field.set this JImGui.input text, and we'll say field.getName plus a colon. So this will basically just be the field's name and make it look a little bit nicer by using our extended function. And then we'll just say string value, and this should be a capital S, which should, if we look at this, this returns a string for us. So basically what ends up happening is we get the string that's currently there. Then if it changes, it returns a new one, and we just set the field automatically. So if we run this now, we should be able to click onto this pipe, and you can see that if we click on the pipe component, we get connecting pipe name here. It's squished a little bit. You can move that over if you like. We'll call this entrance 1, and we'll call, or actually I guess we should call that exit 1, right? And we'll go ahead and we'll rename this pipe to entrance 1. And then we'll go ahead and rename this pipe to exit 1 so that we have that name set properly. And we'll say this guy's connecting pipe. If we go back into the pipe component, we'll name his pipe
to entrance 1. And just for fun, I'm going to set this as an entrance, and I'm also going to set this one as an entrance. So if we set both of those as entrances and then we hit play, I should be able to click down, and it's not working yet, so we have some bugs that we need to work out. And on second thought, that actually is working for me. What my guess is that we have the tolerance vector a little bit too high, and it doesn't always register that Mario is actually hitting the pipe. So you could do some more fine tuning to get an entrance tolerance vector that works a little bit better. But if we run into the pipe from the side, he doesn't go through it. If we run into the pipe from this side, he doesn't go through it. Only if we hit it from the top, and apparently we get an appropriate entrance vector. So what we could also do is if we check the pipe and we uncheck is entrance, we should no longer be able to go into it. So no matter how hard you try, Mario will no longer go into the pipe. We could test this with all the pipe directions, but I'll leave that up to you guys because this should be working properly for all of them. Like I said, the one bug we have is the pipe entrance does not always fit perfectly. Now, one thing I am going to say is let's go into key controls because this has been bothering me for a while. We need a way to easily edit our game world, which we do not have right now. So if we go into key controls, we can add some more key bindings. Let's say if key listener dot key is key pressed GLFW key page down and debounce is less than 0, we will be adding a debounce, and this is just that you can hold down keys and move items for several frames. We're going to bind the page down and page up keys to change the Z index. So we'll just say debounce equals debounce time. And let's go ahead and add those variables very quickly. So if we just scroll up to the top, we can say private float debounce time equals 0.2f. Private float debounce equals 0. This means that if you press down a key every 0.2 seconds, it will repeat that key press, which is what I thought was a good value. If you don't think that's good, that's fine. Change it. Inside here, we'll simply say debounce minus equals dt so that we can keep track of that time. So back to the page down. So if they press page down, we'll say for game object go in all the active game objects. We'll simply say go.transform.zindex minus minus. And we'll want to do basically the same exact thing, except if they're pressing the page up key, we want to change their z-index to 1 higher. So we'll plus that z-index. Otherwise, we want to add in a couple more key bindings. If they press the up key, so not the page up key, but just the up arrow key, then we're going to go ahead and instead of moving the z-index, we'll say go.transform.position.y plus equals settings.grid height times multiplier. And this multiplier will basically just be like shift. If you're holding shift, it will change it so that you're moving it in smaller increments, which is how we can reposition those pipes. Good. And we'll basically do the same thing, except for the left arrow key. We will say .x minus equals this. And for the right arrow key, we will say .x plus equals this. And lastly, we will say for the down arrow key, .y minus equals this. Now that multiplier value is pretty simple as well. We can just go up to the top and we'll say float multiplier equals key listener dot is key pressed GLFW key left shift. So if the player is pressing the left shift key, we'll move at 0.1 increments at a time. Otherwise, we'll move 1.0. So this means we'll move a tenth of a grid space if they're holding shift and the full grid space if they are not. So if we run this again, we should be able to move these pipes into a better position. Just click it, hold shift, and then press the arrow keys to move it into a better position. And you'll see that you can actually move the pipes into a good position. And I'll move it directly into a grid space just so that we can see that. This is also good too because now you can select multiple blocks and just move them with the arrow keys. Move them a few spaces if you want, just to give your world some variance. So if we go ahead and run this again, you can see that we've sort of got a working game. And I still have this pipe off, so that's why we can't go through it. So I'm just going to remark that. Also too, if we add in a couple decoration blocks, say we wanted a bush here, which you could also create as a prefab to make this easier on yourself. You could have like decoration prefabs and all that stuff if you wanted to. I'll go ahead and collect all those and then move them down by pressing the page down key. Now they're behind Mario. And if we were to select all of them again and hit page up twice, this will make sure that they are in front of Mario. I'll grab that one behind him, press page up twice. Now it's in front of Mario. So this is really turning into a full-fledged level editor that you can use with your game engine to create some pretty complex levels. And you can, of course, add more key bindings and add any other components you want. So that's going to be it for this tutorial. In the next tutorial, we're going to work on the camera movement. So we'll add it so that when Mario moves a certain amount to the right, the camera moves to the right and then it stops moving. And we will also change the background color to the real Mario sky blue. In the last episode, we got to the point where we have some better editor controls, and we can also play as Mario, kill the Goombas, and enter into a pipe if we want to, and travel through that pipe to the connecting pipe. So we've basically got a working Mario game, except we have one big problem. If I try to run to the right, yeah, he just kind of falls. So we need to fix that. Let's take a look at a drawing to see how we can get camera controls working in our game. And then once we get a little bit of an idea of how it will work visually, we'll go ahead and implement it in code. All right, so I have a drawing here just for illustrative purposes because clearly my drawings really stink. So what we have here is the camera view represented by this red box and our game world represented by the black objects. And we have our player and the Goomba. What we want to happen is if our player passes a certain threshold of the screen, say like 3/4 of the way through or halfway through or some other distance, the camera starts to move with the player. But then if the player goes back and he crosses behind this line, the camera should just stay still and it shouldn't move beyond that. How can we implement this? Well, if you're thinking like a good programmer, you should very clearly have some ideas in mind. Now, my first idea is we just get the camera in reference in the player controller and we move the camera from the player's controller. So we basically could have another component which has a reference to the player and to the game camera, and this component will control the camera's movement. You could do it within the player itself, or you could do it within a separate component completely. I think it would be good to have something called a game camera, which sort of handles both responsibilities. That way we have it separated from the player, which is sort of a different idea entirely. So this game camera can basically just say, hey, when we pass this position in the camera, when the player gets to this point, we should start moving the camera to match the player's position. What is this position though? Well, if we look at where the camera is, we can get the camera's X and Y coordinates, which point to this corner right here. So anyways, we have the position of the camera, we have the position of the player in regards to like this corner right here. This is the player's XY. Well, if the player's X is greater than the camera's X plus, let's say this is 3/4 of the camera's projection, then we just match the camera's position to the player's position. So how do we get this projection? Well, that's embedded within the camera itself. Remember, we set up a projection matrix which defines how wide this camera should be in world coordinates. And I believe this is 6 world units, and the camera's height is 3 world units. And so we can basically set this to like 4 world units right here, and that should give us a pretty ideal scenario. The other thing we will be doing is we'll be storing a clear color within the game camera. This clear color will change the color that we see in the background right here, because you'll remember that GL works on the basis that we clear the entire screen every frame with a certain clear color, which we can store in the camera, and then that will set the tone for the game. And we'll just set this to the Mario blue, and then when we go underground, which means the camera's Y level is less than 0, then we'll change it to black. This sounds like a pretty good starting point to me, so let's go ahead and code it and see if we can get it working. All right, so I am back inside of our game engine code, and you can see I'm inside of editor camera. So we already have the idea of a camera. Let's just add another camera in here, and we're going to call this the game camera, which will just be our game camera component, and this runs during the game. And we'll say that this extends component. And like I said before, we will want a reference to our player. So we'll say player, and that will give us a good handle on what to use. And then we will also want a reference to
the camera, and we'll call this game camera. Really, it's just the scene camera, whatever you want to call that. That makes the most sense to you, but it is just the camera. And then we'll have this variable, which is going to be called the highest x. And this is sort of going to keep track of where our camera is in relation to the world, right? We only want to move it if the player passes a certain threshold. So this will enable it so that the camera stays still until the player moves back past that threshold. And we'll set this to the minimum value of a float so that it gets set to whatever the camera's value is at the start. Then I'm going to add in a variable, and we'll call this the underground Y level. And we're going to set this to 0.0. This will just make it so that we can change the camera's clear color when the player goes underground. And we can actually change the camera's level when the player goes underground too. And then we will have a float the camera buffer, and we'll set this to 1.5f. We will use this camera buffer to basically determine how far underground we should go for the underground Y level. So basically this is just, normally the camera is located here, but when we go underground, we just want to make sure the camera is located all the way down here. So like say this was the ground, we just want to move the camera down to here. Put visually, normally the camera is going to be pointed up here, which is where the ground level is. But when we have the camera buffer, it's going to be pointing down here so that we are actually looking below the ground. So that is all that is. And then we're also going to have a private transient float player buffer. These aren't very clear names. I could probably come up with something similar, but this is basically just the player height. So this makes sure that we get down far enough to avoid the player whenever we're checking to see if the player died or something, or if he's underground or not. And then we'll have a vector for f. This is going to be our sky color. And this is going to be a new vector for f, 92 over 255. And I just looked up what the Mario sky color is and set it accordingly. 148 over 255. And then 252 over 255. And then, of course, just 1 since we want to have an opaque color. And then we'll have a private vector for f, underground color, which this one's easy. It's just a new vector for f0001. So this one is just black. So very simple color. Then we'll create our constructor. This is going to take in a camera, which is the game camera or the scene camera or whatever you want to call it. And we'll say this dot game camera equals game camera. And then we'll have an override, public void start. And by the way, you could have this game camera be set inside the start method, similar to how we're going to get this player component. So the way we're going to get the player is by creating a function we don't have yet. We'll say this dot player equals window dot get scene dot get game object with, and we're going to get a game object with the player controller class. This is probably the best way to do this because it makes sure you don't have any typos if you're like getting it by name or something. And it's just a little bit cleaner. And this will find the first game object with this class, the way we will implement it. So how would we implement a class or a function like that? Well, let's just go right below this method right here, and we'll put it right here. We'll just say public t extends component. So we're going to sort of do the same thing we did earlier for getting a certain component, and we're going to use the same idea. So we'll say game object find or get game object with, and this will take in a class t, and we'll do class with the z's so that we don't use a keyword. And then we can say for game object go in game objects if go.get component class does not equal null, we'll return that game object. Otherwise, we return null. You could probably simplify this sort of how we have some other functions in here that are simplified, but this works. It just iterates through. It's going to be slow, but it'll find the correct game object and return it, which is what we want to happen. So let's go back into game camera. Now we have both of those set, and we'll say this dot game camera dot clear color, which we don't have yet, but we will, dot set sky color. This will set the camera's clear color, which is a variable we'll introduce in a second, to the sky color. And then we'll say underground Y level equals this dot game camera dot position dot Y minus this dot game camera dot projection size dot Y minus this dot camera buffer. And this will basically just set a Y level that looks pretty good
for the game camera. And I'll move this to a new line so that we can see that. And that should be good for the start method. We've sort of initialized all the variables. Let's go into camera real quickly and implement this clear color. So if we just go into camera, we can simply add in private vector for f clear color, which is a new vector for f, and we'll set it to white initially. Import that. If we go into our window, we can go down to where we clear the color, which is somewhere down here inside the loop. Which, yep, right here. We clear the color right here. Instead of clearing it by this, we can clear it by whatever the camera is. And the easiest way to do that, I think we can just get it based off the scene. We can see scene.camera.clearColor. Yeah, so that'll work. So we'll say vector for f clear color equals scene.getCamera or .camera.clearColor. And we'll have to make that public in a second, which will be fine. I'm just going to import that as well. And then we'll say clearcolor.x, or can we say r? No. So x clearcolor.y, clearcolor.z, and clearcolor.w. Okay, and that should clear it to whatever the camera's clear color is. And if we just click on this, we'll make that a public variable, which should be fine. Then if we go back into the game camera, we no longer have a problem, and we should be rendering with whatever the camera's clear color is set to, which will be good. Okay, next we'll override and implement a update method, which will do exactly what we talked about, right? We'll say if the player is not null, meaning we found a player, and the player.getComponent player controller.class is not null. That's a little bit redundant. It should have the component since we looked for a game object with that component, so I'm not going to reintroduce that here. We're going to say and not player controller or player.getComponent player controller.class.has1, and we'll implement that very quickly. For now, it's not going to do anything, so we can simply just say public boolean has one, and we'll just return false. We implement this so that at the end of the scene, when we play the little win animation, and I'm just going to move this down. When we play the little win animation, it's not going to change the camera's position because we want the camera to stay still at the end of the scene, and this should do that for us. Anyways, once we figure out that we have a player, we'll say GameCamera.position.x equals math.max player.transform.position .x minus 2.5f and highest x. And then we're going to say highest x equals math.max highest x and GameCamera.position.x. So what's happening here? Well, what we're basically doing is saying the player could be anywhere from, say, this is the left side of the camera, this is our player, and this is the right side of the camera. Okay? And then say this is where we want it to start moving, right? When the player hits this point. Well, what we do first is we say player, the camera's position x is equal to the player's transform minus 2.5. So that's going to be somewhere back here since we haven't hit this point yet. So it's going to be somewhere back here, or highest x. Well, what is highest x? Well, that's going to be the highest x or the game camera position.x. So that will basically give us this point here or this point here. Clearly, this point is higher, so the camera will just stay still. But then once the player passes this point, we'll say take the maximum of this and highest x. Well, now the maximum is right here, right? Because this is where this is. So highest x will now choose this since it is higher, right? The game camera's position will be here, and then the camera will move forwards, and it'll continue doing sort of this loop. It's a little convoluted, but it works. Next, we'll say if player.transform.position.y is less than negative player buffer, meaning the player has fallen below the ground for whatever reason. We're going to assume it's because they have not won, so they're not dead, but it's because they're actually below ground. Then we just want to say this.GameCamera.position.y equals underground y level, so that we move the camera down. And then we'll say this.GameCamera.clearColor.set underground color. So we set the color appropriately. Then we'll say else if player.transform.position.y is greater than or equal to 0. Well, then they're at the regular level. So we could say this.camera.position.y equals 0. This.GameCamera.clearColor.set sky color. Okay, So with all this in place, it should work, but we still need to add this to our game scene, right? So let's go into our level scene initializer, not level editor, and we don't actually have a level scene initializer. So this is a good point. The easiest way to get a different camera into the scene is basically just by getting a whole new scene initializer. Right now, if we use this one, we're still going to have all the components that shouldn't really be there when we're in runtime, right? If I hit play, I can still click on objects and it's technically selecting them. We're not seeing it because we have it running through the update loop, but all of this stuff is still there and we don't really want that. So let's create a new scene initializer just so that we can differentiate between the editor runtime and the game runtime. And we'll call this level scene initializer. Now what I'm going to do is I'm going to copy this and just paste it over because it's going to be basically the same thing with a few differences. So first of all, we're just going to change the name of this to level scene initializer and change the name of this one as well. Secondly, we're going to leave all the load resources because we do still need that, but we're going to remove this ImGui window because we do not need to use ImGui at all. And then if we scroll back up, oh, and it looks like we actually need to implement the ImGui method. So we'll go ahead and implement it, but it's just going to be empty because we don't really care what goes on in there. So we'll leave that empty and then we'll scroll back up and we're going to go ahead and we don't need any gizmos. So we can remove this. We're going to go ahead and say we don't need this level editor stuff. So we can go ahead and remove all of that, which is actually going to remove the grid lines and everything for us automatically. And then one thing we might want to do is I'll keep this and this will be the game camera. And so we'll just have this game camera and we'll say level editor stuff, which I'll change the name in a second, .add new game camera. This way we get a game camera and it says it needs a reference to a camera. So we'll just say scene.camera, which should give us that camera. And then we'll go ahead and change the name of this to just like camera object, just so that it's clear what this is. And then I will paste over all of this and we'll paste over that. And we actually don't need the sprite sheet anymore or really that either. So we can just say right in here, sprite sheet, and just initialize these inline and then game object. And last thing we'll want to do in here is make sure that we say game or camera object dot start. We have to start it manually because we're adding it to the scene right here. So we just need to make sure that we start it before the scene actually starts. Anyways, once we get that done, we can go into the window and fix up one last thing, which is inside of our event callback, which we have on notify. When we start playing, we actually want to switch to level scene initializer instead. This will just make sure that we switch to the level scene, which means we get a different camera. And you'll see the camera started moving then too. So we get a different camera. The camera color should switch. So we'll have to look into why that's not working. You also notice it looks like the game view is lowering, and that's because we're losing this window since we are switching into game mode. You could fix that if you wanted to so that the game window is still there. But you'll notice that now we can move, or we almost can move. We have to change one more thing up, which is inside of our player.die. So if we go into the player controller, I had forgotten about this. We'll also have to fix this dying method, which is where we change the scene. We just want to change to a level scene initializer, and that should be good for us. So we'll just run that one more time. And now if we run and we die, so you'll see the camera just move there, but if we die, we're still in the game mode, so we can still move the camera. And if we drop, you'll see that the camera actually moved down there. That's because it believes that we're underground. Let's see what's wrong with the clear color and see if we can get the clear color working very quickly. And I know exactly what the problem is. If we go back into the window class, you'll see I'm setting the clear color here, but that was completely unintentional. We actually want to clear this color to 0, 0, 0, 0, because this is not the clear color I was thinking. This is for our picking texture, right? We have the picking texture enabled. We should be doing this clear color to the camera's clear color, which should give us the desired effect. So we'll say clear color.x, clear color.y, clear color.z, clear color.w. Okay, now if we run it and we hit play, we'll see that we get a blue sky color. And if we have a suicidal Mario who decides to jump off the edge of this cliff, you'll notice that it turns black down here and he continues falling. Now, why do I have the camera turn black like that? And I'll also mention how we can fix this issue with the grid lines too in the future. For now, we'll leave it as it is. But why do I have it turn black like that? Well, the reason is because if we add in, say, a prefab for a pipe going down, and I'm going to add it in right here because I believe this is where the underground level starts. We can adjust as necessary. We will name him exit pipe 1, which I believe is what we think the connecting pipe should be. So if we look at this pipe, let's just make sure that should just be exit 1. So we'll just rename him exit 1. Now, if we hit play, we go through this, you'll notice that we sort of pop out of the sky. So I don't have that set quite right. I'll move this down a little bit further and let's try this one more time. Okay, there we go. So now you'll see the pipe is at the top of the screen and these blocks are still not quite at the bottom of the screen. If we want to get it perfect, we can sort of go down here and then just move some of these down so that we can see that appropriately. And then we'll go ahead and move all of these blocks down as well. And we'll move these blocks down as well. And lastly, these ones, just that we're consistent. Okay, now you can see that we kind of have all of this stuff set up properly. And the debug drawing lines, like the grid and everything, is all way whacked up. And that's just because of our debug draw method, which we will have to fix. But this just means that now we have a way to get Mario down to the lower level. So now as you're building your Mario level, you can build with the notion that there's this underground level where you can have pipes lead to, and you could do the same thing by having another level and say this is the water world and so on and so forth. So that's sort of the idea. Now, this is really bothering me, the fact that our debug lines are not showing up properly. So let's go ahead and fix that very quickly. First of all, let's go into debug draw. And I'm going to increase max lines from 500 to 3000. I don't know why I have the maximum there, honestly, because it really doesn't matter that much. Now you can see we get the grid lines because we're not running out of room, but they're still kind of messed up. You can see that it's not quite lining up correctly. And the reason for that is if we go into grid, we have to fix a couple of things in here. So first thing we're going to change is remove this -1 from these guys because we were just off by 1 in terms of this error. And then right here, if you just add in 5 times the grid width and 5 right here, 5 times the grid height, that seemed to be a good value for me. You can see we have it ×2 for now. I don't think that's really necessary, and 5 worked better. So that should just increase the number of vertical and horizontal lines we're getting, which should give us the correct lines. And if we run this again, you'll notice that as we zoom out and zoom in, we get a good amount of grids. Like the grid is covering the whole screen, which is how it should be. I really should have fixed this a long time ago in the episode. We'll do one more optimization, which is we'll go into debug draw and we'll cull out lines, or we won't draw the lines that aren't on the screen. So let's just go to our add line 2D method, which is right down here. And we have this if it's greater than max lines return. And I'm going to go ahead and just expand this a little bit. So this is going to become kind of a convoluted line of code, but it will work. First of all, we're going to say camera equals window.getScene.camera. So we're going to get a reference to the camera so that we can figure out how big our projection size is. And then we're going to say vector2f camera left. So the left side of the camera is new vector2f camera.position .add new vector2f -2 -2. And this should give us like a bottom left corner of the camera that's kind of off screen. That way we don't cull out all the lines, just some of them. And then we'll get camera right, and this will be a new vector2f camera.position .add a new vector2f. And this is going to be the camera.projection size multiplied by the camera's zoom level. So that way we can see how far it zoomed out. Add new vector2f 4.0 4.0. And this very long line of code is basically just making sure that we get the camera's position and then we add the camera projection size times the zoom level, which should give us the appropriate camera projection size, plus this 4.0, which is just like a buffer so that we have a little bit extra off-screen room for extra lines. And then we're going to make this line way more convoluted by saying, actually, we'll do this a little bit simpler. We'll say Boolean line in screen, or we should say line in view, equals, and we'll say from.x is greater than or equal to camera left.x, and from.x is less than or equal to camera right.x, and from.y wrapped in parentheses, from.y is greater than or equal to camera left.y, and from.y is less than or equal to camera right.y. So we basically check and see if the left side of the line is in the bounds of the camera, or we're going to do essentially the same thing. I'm just going to copy this, except for the to line. So we'll check and see if either of the endpoints of the line are in the camera's position, and I'm just going to replace all of the froms here with to. And so if either of the endpoints of the line that you're trying to draw is inside of the camera's viewport, then we'll draw it. So we'll say if the line's dot size is greater than max line, or the line is not in view, then we're just going to return and we're not going to draw it. So now, if we run this again, you'll see that as we zoom out, we get lots of lines. And what ends up happening is actually these debug lines, you can't really see it, but as soon as this Goomba gets off screen, we stop drawing the circle around him. So that way we have room to draw more debug lines and we won't run out of room, which is nice. That's what we want to happen. So that was just a quick optimization I didn't plan on adding in this tutorial, but it works. And now we've got sort of a pretty good Mario game going on. Like if I just delete that and then we duplicate these blocks, move them over with the arrow keys, you can see that I can start building out a level. I'm going to move this pipe over too, and if I just hold the right key, it'll keep moving it in small increments. And then you can see that if I press play, it's sort of going to move Mario across. I can get this thing. I can go down the pipe if we hit it at the right position. And Mario's off screen because the pipe's to the left of this, but you'll see that Mario actually is there when I keep going. And if I were to jump off, we could make it so that he dies and continue working from there. But yeah, Mario is really coming into shape, and we've got a level editor that's working out pretty good. I hope you guys enjoyed this. If you did, please hit like and subscribe, and stay tuned for the next episode where we go over Turtle AI. So we get the Turtle AI working where you can jump on the turtle and bop its shell back and forth. All right, guys, I'll see you next time. In the last episode, we got to this point where we basically have Goombas working. We can also go through pipes and stuff. I just don't have any on the screen right now. Actually, I do. So we can go through pipes and stuff if we hit it at the right angle, which is kind of difficult sometimes. So we can fix that up in a later episode. But for now, what we're going to be adding in are turtles. So Mario has the turtle AI, and that is what we will be working on next. So first of all, let's go into our level editor scene initializer. And we basically want to add our turtles to our ImGui panel so that we can actually add them to the scene. So right over here in our loop, right below where we're adding the Goombas, I'm going to add in a turtle. So first of all, we have to get the sprite sheet, which is asset pool.get sprite sheet. And this is located under assets/images/turtle.png. Once we get that, we can basically just copy all of this stuff. And it's almost the exact same thing, except for the sprite, we're getting the turtle. And we're going to get the 0th sprite, which is just the first sprite in the sprite sheet. And then for the game object, we're actually going to say generate turtle, which does not exist, but it will. So once we have all that done, we can go into our prefabs and basically just add in a function to generate a turtle. And for that, I'm going to copy the Goomba because it is almost exactly the same with just a couple of differences. So we will go ahead and copy that, and we'll call this generate turtle. So now that we have this function, we just want to first of all get turtle.png instead of that sprite sheet. And we'll call this turtle sprite, and we will call our game object a turtle. And we also need to change, which we don't usually do. So first of all, we have to change that. But we're also going to change the scale because turtles are slightly different scale. So we're going to be using 35F for the Y, which will give us, which will basically just give us a nice size turtle because they're a little bit bigger than the Goombas vertically. But yeah, and then we'll also use index 0 for the sprite just so we get the correct sprite sheet. And we're going to have a walk animation. We're going to use the same animation length for this, except we're going to be using frames 0 and 1 for this. We want this to be looping, and then we will also have a turtle shell spin animation. So we'll call this turtle shell spin. This is when the turtle's spinning around on the ground. This will just consist of one animation, so we're not even going to actually pretend it's spinning. It's just going to be one frame, and this will be index 2, and it will not loop. Next, we'll add everything to the state machine, so most of this will basically be the same. We're going to keep this as squash meat just because it makes sense, and I guess we could change the name of this to like turtle shell, but I'm just going to leave it for now, and we will add the state machine to our turtle. Then we're going to add a rigid body like we did here, set it to dynamic. All this stuff should basically be the same, and then we're just going to add this to the turtle instead. And then we're going to have a circle collider, add this to the turtle instead. And a couple of things are going to change here too. The radius is actually going to be 0.13f because it's just a little bit bigger. And then we're also going to add a offset. So we're going to say set offset to a new vector 2f, 0 minus 0.05f. And this will give us just a slight offset for our turtle because we need that. And then we will go ahead and add a component to the turtle, but it's not going to be Goomba AI, it's going to be Turtle AI. So mostly the same as the Goomba, except one key change, which is going to be the component that controls his logic. So let's go ahead and actually create that component now. So if we just go into components and create Turtle AI here, we can go ahead and say this extends component, and we'll go ahead and implement this now. So we're going to need quite a few variables. Most of them are going to be pretty similar to the Goomba once again, so it shouldn't be any surprise how this works. The main change we're going to have is just sort of the state. So we just have to manage some different things when the turtle's in a spinning state. So we'll have a Boolean going right, which is false initially so that he starts going left. Then we will have a transient rigid body, RB, which is just a reference to the rigid body. We'll have a transient float walk speed, which I'm going to set to 0.6f, which was a good speed for me. And then we will have private transient vector 2f velocity, which we'll just initialize to an empty vector 2f. And we also need to import that. So I'll import that very quickly. Then we're going to have acceleration. So these are just the standard things, also empty. And we're also going to have a terminal velocity just to limit our speed in the horizontal and vertical direction. And so I used for this just a new vector 2f, 2.1f, and 3.1f. So that should be good. And then for a few more variables to keep track of some state, so we'll have a Boolean, which is on ground. This is false initially, just to tell us if he's on the ground or not. We'll have a private transient. Boolean is dead, which is false because he should be alive at the start. We'll have a transient Boolean is moving, which basically just lets us know if he's moving, and he could be moving while he's dead, which means he's spinning as a shell, or he could be moving while he's not dead, which means that he's just walking. So it's important to know the difference between those two, which is why we have that. And then we'll have a private transient state machine, which is just a reference to our state machine. And finally, a float moving debounce equals 0.32f. And this will just be so that when we bop him on the head as Mario, if we kind of get 2 frames caught there, it won't act like we hit him and then we hit him again. So like basically when you jump on a turtle, if you jump on that turtle shell again, it'll start moving, and we don't want that to happen. So we just add this debounce to make sure that we don't accidentally trigger that the first time we jump on it. Okay, so now we'll override our start method, which is just going to get some references for us. So we will say this dot state machine equals this dot game object dot get component state machine dot class. We'll say this dot RB equals game object dot get component rigid body dot class. And this dot acceleration dot y equals window dot get physics dot get gravity dot y times 0.7f. So we'll initialize this to 70% of the gravity. And next for the update method. Most of this should be pretty familiar too, because it should be mostly the same as the Goomba, with just a couple of key differences. So first of all, we'll subtract dt from the moving debounce, just so that we're keeping track of that. And then next we're going to say if this dot game object dot transform dot position dot x is greater than camera's position, and we need to get a reference to the camera, so let's go ahead and do that very quickly too. So let's get a reference to the camera, which we can get by just going get scene.camera, and we'll import that. And if the game object is greater than the camera's position.x, and I'm going to move this to a new line because this is going to be kind of big, plus the camera's projection.x times the camera's zoom What does this mean? Well, this means that the turtle is to the right of our camera view. If the turtle is to the right of our camera view, we'll just return. This will make sure that the turtle doesn't start walking left until we actually get into view, which is how the Mario game works, and that's why I implemented this in here instead of making this a broader feature overall. Next, we just need to check our state and update our speeds accordingly. So we'll say if we're not dead or we're moving, so basically we're either walking or we're just moving. If we're going right, then we can say velocity.x equals walk speed. And we'll say else velocity.x equals negative walk speed. So that should just set our speed to the appropriate value. And then we'll say otherwise velocity.x equals 0. So if we're not moving and we are dead, then we set the velocity to 0, which means that the shell should just sit there. Next, we're going to say check on ground, which I'm literally just going to steal from our Goomba because it's basically the same thing. So I'll just copy that, which I conveniently had highlighted, and I'm going to paste it down there. And the only thing we're going to change is this value right here, which we're going to use minus 0.2f, which should give us the appropriate values, and everything else should be fine. So basically we check on ground. That should check and see if the Goomba or the turtle is hitting the ground or not. If we are on the ground, then we're going to say this .acceleration.y equals 0 and this .velocity.y equals 0. Otherwise, we're falling. So we say this .acceleration.y equals window.getPhysics.gravity.y times 0.7f. And you may think it's laborious to do all this manually and stuff, and why are we doing it like this? Well, the reason we do this and we don't let Box2D handle the physics is because we want to have very good control for a game like Mario. There are other games where you want to let the physics handle everything like this, all the physics engine. But for character movements and stuff, it usually looks better when you actually control the characters. So anything that like an AI or your player or anything like that, you control explicitly. Whereas if you have boxes or something like that in the game, you can let the physics engine handle that and everything will feel a lot better that way. So that's why we go through this process. But anyways, we'll say this .velocity.y plus equals this .acceleration.y times dt. And then we'll say this .velocity.y equals, and I'm going to go to Goomba again because it's the same thing as this and I don't feel like writing all that out. And actually, let's just go ahead and copy both of these. If you wanted to be really good, you could probably create a base class and inherit from that base class in all of these, or you could add these to like a static function that all of these types of objects call, and sort of like what we did for the physics 2D here. And that would be a good solution since we are doing the same thing a lot here. And then we're going to add one more thing, which is if this game object's transform position.x is less than the windows get scene.camera.position.x, and I'm going to move this to a new line so that we can see that, minus 0.5f, or this .gameObject.transform.position.y is less than 0.0f. So if the turtle has fallen off the bottom of the screen or he is behind the camera to a certain extent, we're just going to say this .gameObject.destroy. And this is just so that if the turtle shell goes spinning off or whatever, he falls down to another level, we just get rid of him. You might want to change this though, since we do you could have turtles on the bottom left. So you might want to do something like getting our camera controller, which is the game camera, and checking what level it is, which you can see right here. And then basically, or not right there, but right here inside of the game camera, I guess. And then checking to see if the turtle is below that. So basically, you don't destroy it if he falls or if he just spawns in the bottom part. So yeah, I'll leave this commented out for now just because that's probably something you want to encode special behavior for. So I'll just comment that out, but be aware that you do need to add support for that yourself. Okay, cool. So we basically add that in. If he's to the left of the camera, then we destroy it. Next, we want a method that we can call every time he gets stomped on that sets all our values. So if he gets stomped on, we'll say this dot is dead is true, this dot is moving is false, this dot velocity dot 0, this dot rb dot set velocity to this dot velocity, this dot rb dot set angular velocity to 0, this dot rb dot set gravity scale to 0. And this is just to ensure that he doesn't fall down or do any sort of weird movements. And we'll say state machine dot trigger squash me. So if we get stomped on, we get squashed, right? And then we'll play a sound. So we'll say asset pool dot get sound, assets slash sound slash bump dot ogg dot play. Okay, and that should do it. So that'll basically stomp him, and then we set all the booleans, our flags, and we sort of zero out his velocity, which should be good. And next, we're going to override begin collision and I believe pre-solve. So let's go ahead and override this. This will take in a game object, obj, a contact, and a vector 2f contact normal. And it looks like I misspelled something here. So let's go ahead and, or we just need to import that. Okay, so we'll import that, and I'm going to go ahead and copy that as well. And we'll say override public void pre-solve. And I'll just sort of paste that here and get rid of this extra stuff that I copied. Okay, cool. So we now have a begin collision method and a pre-solve method, and we're going to fill these in. So we'll want to see if he collides with the player. So we can just say player controller equals object.getComponent player controller.class. And if the player controller is not null, so we just hit the player, what do? Well, first let's check if we are not dead and the player controller is not dead and the player controller is not hurt invincible. So player controller is not dead and he is vulnerable right now. And the contact normal.y is greater than 0.58f. This should be contact normal. So if we hit the player, we're not dead, he's not invincible right now because he got hurt and he hit us on the top of our head. What happens? Well, then we go into a shell state, right? Because we're not in our shell state since this is dead flag is not set. So we'll say player controller.enemy bounce to bounce the player, and we'll say stomp to stomp ourselves down, and then we'll say walk speed times equals 3.0f, and this will just ensure that we spin faster than we would go walking, which is how the game is too. Like when you're spinning, you go faster. So that's the same thing. Otherwise, if our moving debounce is less than 0, so this means that we've had sufficient time for the player to get out of our way before he bounced on us again, and the player controller is not dead, and the player controller is not hurt invincible, and we are moving or we are dead, not dead, and the contact normal.y is less than 0.58f. Okay, so what are we checking here? We're checking to see if, first of all, this should be an and, if the player controller has had sufficient time to bounce away from us and he's not dead and he's not hurt invincible, and we're moving or we're not dead. So like we're moving or we're not dead, that means we can hit stuff. And the contact normal.y is less than 0.58f. So he hit us to the right side. So what happens if the turtle runs into Mario? Mario gets hurt. So we just say player controller.die. That should do that. And then we can say else if player controller is dead, the player controller is not dead, and the player controller is not hurt invincible. So if the player controller is not dead, player controller is not hurt invincible, and we've passed all of these, then that means that the player has hit us while we are dead or we're moving. And so what we're going to do next is we'll just say if we're dead and the contact normal is .y is greater than 0.5af. So if we're dead and he bopped us on the top, then we'll say player controller.enemy bounce. So we bounce him again. And we'll say is moving equals not is moving. So we basically start moving. If we're not moving, we stop moving. If we were moving because he just bounced on us, then we'll say going right equals contact normal dot x is less than 0. So then we just check what side of the shell he hit us on, and we set what direction we're going to go to the opposite of that. And we'll say otherwise if we're dead and we're not moving. So we're dead and we're just a shell. Then we'll say is moving equals true. So he just ran into the side of us, and we'll say going right equals contact normal dot x is less than 0. And then we'll say moving debounce equals 0.32f to give us time to get out of the way. Okay, so that should be everything for when we hit a player. Otherwise, if we're hitting any arbitrary object, we'll just say math.absolute value. So if the absolute value of the contact normal.y is less than 0.1f, which means we got hit on the side, and the object is not dead, which means we got hit by a valid object, then we'll just say going right equals contact normal.x is less than 0. And then we'll say asset pool.getSound, assets/sounds/bump.ogg.play. And we should actually only play this if we are moving and we are dead. So if we're moving and we're dead and we hit something to the right, then we play the bump sound because we just hit something and we change directions. Okay, finally. And that should actually be good. In the pre-solve, though, we do have one last thing to worry about, which is what if we hit a Goomba and we're moving as a spinning shell? Well, then we have to kill the Goomba. So we'll say Goomba AI, Goomba equals obj.getComponent, Goomba AI.class. If we're dead and we're moving, so we're a spinning shell right now, and we hit the Goomba because Goomba is not null. So if we're dead and we're spinning and we hit the Goomba, then we should kill the Goomba. So we'll say Goomba.stomp, and then we'll say contact.setEnabled false. So that way we just spin right through him. And then we'll say asset pool.getSound assets/sounds/kick.ogg.play. So we will kill the Goomba and play all the correct sounds, and this should be good. Let's go ahead and run this and see what happens when we add a turtle. Fingers crossed everything works right. So if we add a turtle in right here, and you'll notice he's a little taller, but he'll get bumped up to ground level once we actually start. And I'm going to go ahead and just add a block here so we can see what happens. So if they hit each other, yep, he should turn directions, but he doesn't switch directions. So first of all, let's fix that. So right up here, when we're checking which direction the turtle's going, we can just check and see if he's going right. This is when we're seeing which way we should set him. Then we'll just say GameObject.transform.scale.x equals minus 0.25f. We're doing minus because he's to the left in the sprite sheet originally. So yeah, and then we'll say transform.scale.x equals 0.25f otherwise. So this way he should turn around the right direction. So if we play this again, he should turn. He turns. Sweet. So that's good. Let's go ahead and just add another block here so we can test the other features. So, okay, I just bounced on him, so we can't check that. But if I bounce him, he turned into a shell, and then he killed us when he started moving. So that's good. Now let's make sure he can kill the Goomba too. So if I go ahead and just do that, and we bounce it, that killed the Goomba, so that's good. And the last thing I need to check is if we can stop the shell. So if we go ahead and just do that, and if I jump on it, okay, cool. And we can stop the shell too. And I really stink at this too, because I keep dying. So yeah, we basically got a working turtle AI now. He's just kind of working good. And that's kind of weird. Okay, so I guess we were just like, we just kept hitting it, which is kind of cool actually. Yeah, so we're just hitting it there. And then since we're hitting it to the right, we're kind of hitting it before it has a chance to go off. But yeah, that's the turtle AI. And it works just like it would in Mario, doesn't it? One thing I'm going to do too real quickly is these red lines are really annoying me. So let's go ahead and get rid of those. I think if we just go to physics, we have this in here. Yeah. And we're drawing these debug lines. Let's get rid of those because there is no reason to be drawing them anymore. And if we run this again, no more gross red lines. One other thing I'm going to check real quick is if we do this and whoops. Okay, well, that's what I wanted to check basically. So if we hit him and we're invincible, he doesn't really do anything to us. We'll try this one more time just because this is actually turning into a pretty fun game. So if I do that and I bounce it, yep, I'm fine. He doesn't go through me, which is kind of bad, but you know, you can fix that in post and everything. So yeah, that is it for the turtle AI though. I'm pretty happy with the way that turned out. We've basically got a fully working Mario game, okay? What's the only thing we have left to do? We just have to add in the end state, winning. And we also have to add in fireballs. I forgot about that. So we don't have fireballs yet. So if you get the mushroom and then you go ahead and you get a fireball, you can't shoot fireballs yet. So we'll add that in and the win state in the next tutorial. And then we should have Mario done, which is really cool. We've created a game with the game engine. It's working pretty good and you can build levels pretty easily with it. And then maybe I'll do an episode or two just about cleaning some things up with the engine, like some of the debug features. The gizmos don't really work properly anymore, so we could go through fixing that just to get it all working properly. And yeah,